Good morning and welcome to the very first YouTube Live virtual lesson for AP Calculus BC. Today is Wednesday, March 25th, and AP Calculus has the distinct honor of kicking off the College Board's live lessons and AP review sessions that will be airing daily Monday through Friday right here on YouTube. My name is Brian Passwater, and I'm an AP Calculus teacher at the world-famous Speedway High School in Speedway, Indiana, home of the Sparklets. And I have the privilege of teaching some of the most amazing and wonderfully talented and dedicated students I've ever worked with. And I am beyond excited to work with each of you that are listening right now following along. I'm joined today by my good friend and fellow AP Calculus teacher, Tony Record.
Hello, everyone. As Brian said, my name is Tony Record. I'm a calculus teacher at Avon High School in Avon, Indiana. And I want you all to know that we're truly blessed and honored to be able to work with you over these next few weeks. And together we have the best full chance of being successful on your AP exam today.
Absolutely. So before we jump into today's lesson, because it's our first session together, I want to go ahead and share a little bit of information with you to let you know what you can expect over these next 5.5 to 6 weeks, not only in this course, but probably in all your other AP courses that you'll be watching live daily lessons with. Every morning at 9 a.m. Eastern time, Tony or myself, we will be here with you to teach you, review with you, and most importantly, help you prepare for the AP Calculus BC exam coming this spring. For the next 2.5 weeks, we will be covering specific topics that are in the AP curriculum, and every one of those topics for 13 days will include daily lessons that are going to focus on 3 really important things. Number 1, we're going to make sure that we teach you the topics and the concepts that are in the curriculum. Number 2, we're going to make sure that we connect those topics and connect those concepts to the previous things that you've learned throughout the year. And then finally, number 3, we're going to make sure that we connect all of these topics to the actual AP exam, so you can see not just the content and the concepts, but how they're going to appear or help you get ready for the AP exam. With all of the extenuating circumstances that are affecting all of us right now across the country and across the world, the College Board has announced recently that the 2020 exam administration this spring will have some select topics that will be not included on the actual AP Calculus exam. Tony and I will be very diligent about indicating this during our lessons. However, even though we're covering some topics that are not tested on this year's exam, those topics are still highly important, and we do encourage you to engage and learn all those topics if possible in order to be best prepared for future coursework beyond the AP exam. We're very aware of the AP exams, and we're very aware that they're coming up around the corner in a few short weeks. And so every single lesson that we cover over the next 6 weeks, whether that topic is being tested or not, will be designed to help you prepare for this year's exam as well. So even the non-tested topics will include many strategies that are connected to the AP exam, and a lot of the previous content will be intertwined and reviewed along the way. So that way, every single session that you attend on here will get you closer to success on the AP exam. Following that initial 2.5 weeks that we're starting today, where we cover selected topics each day from units 9 to 10, we're going to start to transition into a full 3 weeks of AP exam review and prep. Tony and I are both extremely ecstatic to be working with you each day, and we hope that you find each of these sessions to be helpful, enjoyable, and beneficial to you. One last comment I want to share before we jump into our lesson today. If you look down in the comments of the YouTube channel under this video, you should see a link that has a link to some resources. This link will connect you to all the resources that Tony and I will be using over these next 6 weeks during our sessions. Feel free to click on that link. It'll be the same link for every video. It's one link, and in there you will see the materials that we're doing, and then following each session, you'll see answer keys typed up for the sessions that we cover. So feel free to download those materials or print them out. That way you're able to follow along, take notes, and practice with us for the AP exam. So let's go ahead and get started, shall we? So every single one of these sessions will start with a short warm-up, and the warm-up will be something that we typically covered in the previous lesson to get you ready for the upcoming lesson. But since this is our first lesson, let's start with this. So today's warm-up says for any time t greater than 0, we have a particle p moving along the x-axis with position x of t, and x of 0 is 0. The velocity of particle p can be modeled by v of t, and it's given in the graph above. And during the same interval, we have another particle, second particle q, that's moving along the y-axis with position y of t, and it's known that y prime is less than 0 for all t greater than or equal to 0. And there's some selected values for y of t given in the table above. So the question is for our warm-up, at time t equals 8, determine if particles p and q independently are moving toward or away from the origin. So in this warm-up already, we can see a lot of things going on. This is a really good example of what you might see on the AP exam in terms of connecting representations, connecting different functions, and connecting ideas. This is a question that's from earlier in the year that would be typically an AP course, but also on the BC exam. So what we'd like to do on these warm-ups is give you a few minutes to think through them, process them, and see if you can sketch out or start to solve some of the problems. So I'm going to go ahead and turn this timer on, give you about 2 minutes if you have a chance, and either see if you can figure out the problem, work it out, or if you're not 100% sure, spend the next minute and a half trying to think through what the important information would be and how you might start to tackle a question like this that has so much information and so much stuff going on. So I'll give you about a minute and a half, and we'll work through it together. So before we jump into working this problem out together, I want to point out a couple of things. I think as you start preparing for the AP exam and getting closer and closer and closer, one of the things that you will notice if you haven't already is that the AP exams do a really good job of testing your conceptual understanding. You'll probably hear me and Tony use that phrase quite a bit in the next 6 weeks. Because college work and universities and colleges around the country want to know more than if you can just compute or solve a couple of problems. They want to see if you truly understand the ideas, the concepts, and the underlying theories that are going on in the topics that you're learning. And so you see these questions that do a lot of connections. And at first they seem daunting if you haven't done any problems like this, or it's been a while since you had a chance to do these problems. And so I really want to encourage you, when we have a chance to do a warm-up or an AP practice problem at the end of today's lesson, or even the examples that we do throughout the lesson, really try on your own as we're doing them and giving you time to start them, and try to see if you can have a way that you solve them or start them out. Because once you learn how to sort of break down the problem, figure out what's important, and get some of the strategies that Tony and I will share with you these next 6 weeks, I think you're going to find yourself getting better and better each day, getting better and better at solving problems that maybe in the beginning of these sessions you wouldn't feel comfortable doing. So we're going to go ahead and kind of break this problem down together. And so what I'm going to do is highlight a couple pieces of information, which I think is a really good strategy. So when you're working through these problems, start realizing that we have a couple different things that are going on. Number one, we have this idea that we have 2 different particles, right? So we have particle p, I'm going to underline that, and particle p is moving along the x-axis. So I like to imagine you've got x-axis here, and particle p is moving along this axis back and forth somewhere. This will be for particle p. And then we also have the second particle q that kind of gets introduced later on, and it's not moving along the x-axis, it's moving along the y-axis. And so I'm going to put this particle q in red, and so now I have sort of this y-axis go up and down, and this is going to be how particle q is moving. So this is particle q, and then the horizontal x-axis is going to be particle. And so we have these different particles moving along different axes. You notice I put them separately because in calculus AB, we kind of treat particle motion only on one direction, one axis. But today we're going to look at is how we combine these 2 things into one coordinate system through the idea of parametrics. So what do we know? Well, I'm going to start with particle q because I think it's going to be easier to solve. We know a couple of things. We know the position is given in this table. So we have a table of values, and in that table, these are position values for particle q, right? And we want to know at time 8 specifically whether the particle is moving toward or away from the origin. Well, what do we have to know to answer that? Sometimes students say, well, I want to know if it's moving toward or away from the origin. I only have to know which direction it's moving. Is it moving left or right? Is it moving up or down? Is the velocity positive or negative? The problem with that is you can be moving up away from the origin or up toward the origin. We have to know more than just which direction you're going. We have to know where you are as well. We have to know where you are plus which direction you're going. And those 2 things combined will allow us to know whether you're moving toward the origin or away from it. So for particle y at time 8, which is given in the problem, we can see in the table we have this value right here at time 8, and we actually know that at time 8 particle q is at -4. This is the position. So we know that the position is at -4 at time 8, and we know from the original problem that y prime is less than 0. If we think about these connections, we know that y of t represents the position of the particle, and then with particle motion, if we take the derivative of y, or the position, that ends up giving us the velocity, and if we take the derivative a second time of position, that will give us the acceleration. So if y prime is less than 0, this means that the velocity of particle q is less than 0. And since particle q is moving up and down the y-axis, a negative velocity indicates that particle q is moving down. Well, we see the origin right here. So we're starting at -4 and moving downward. This is going to indicate to us that particle q is moving away from from the origin. Now let's go back to particle p. It's a little bit different because we know particle p, we don't have the position at time 8, but we do have a velocity graph for particle p. So now we get to connect another idea from earlier in the year. So hopefully you're already starting to see how, even though if we cover a topic that may not be tested on the exam, we're going to be making a lot of connections because all those previous topics that you learned that are going to be tested on this year's exam are really embedded, and those are the things that drive and help us to build on these new topics. And so each one of these lessons that Tony and I are going to cover are going to be really rich with built-in review, exam prep, and getting you ready for what you're experiencing this year, but as well as beyond this course. And so I need to figure out what the position of particle x is at time 8. Well, if you might remember, we have this ability to create any accumulation function using the funnel theorem calculus. That if I want to know the x position at time 8, we're going to have to use an initial position that we were given, which by the way we knew that x of 0 is 0. So x of 8 is going to be x of 0 plus the integral from 0 to 8 of v of x. And we know that x of 0 is 0. So now we're going to sort of finish out this problem. We just have to figure out the integral from 0 to 8 of the velocity. Well, luckily they gave us a nice velocity graph. So we know that the integral from 0 to 8 is just the signed area between the velocity graph and the x-axis from 0 to 8. And so as we kind of build this up, we get this little region right there. So the integral from 0 to 8 of the velocity is going to be the signed areas of those three shapes. Thankfully for us, all these functions are linear, so we can figure out the area of those using some basic geometry ideas. So I'm going to right here below here, I have a little more space, and we have the integral from 0 to 8 of the velocity of particle p dt. And you can break up these areas however you want. Some of you might recognize this first little region right here is a trapezoid. Some of you might be more comfortable thinking about this as a rectangle, a square, and a little triangle. Either way is going to be fine. I'm going to do it as a trapezoid because it allows me, number one, to get some practice using some trapezoidal approximations. And number two, I can do this area in one formula instead of breaking it up into two, which means fewer calculations, fewer numbers, fewer chances for mistakes. So this first area here is a trapezoid, and our area of trapezoid is 1/2 the height of the trapezoid, which we can see in this case is 1 times the quantity of the sum of the two bases, and our bases are going to be the parallel sides, so it'll be 1 plus 2. Then I get to the second region here, and we see it's a triangle, and the base of the triangle goes from 2 to 6, and the height is 2. But notice this triangle is beneath the x-axis, so there's a bit of misconception that happens a lot. When we say the word area is always a positive value. Area is positive by definition. We're talking about a geometric shape and how much space something can hold. However, when we're doing definite integrals, especially with graphical representations, we typically call this the signed area, meaning since this part of the shape is below the x-axis, we're going to give a negative value we compute it. We're not saying the area of the triangle is negative. We're saying that the definite integral for that portion is negative because we're basically losing accumulation there. So we're going to do a little minus here because it's below the x-axis. And a triangle, the formula is going to be 1/2 base times height, so it's going to be 1/2 4 times 2. And then finally for our last portion here, we have another trapezoid that's identical to the first one. So we know the area of that is going to be 1/2 1 times quantity 1 plus 2. Now a little bit of arithmetic here. I'm going to save you some of the details, but if we were to compute all these, we would end up with -1 for our integral, which means that x's position at time 8 is going to be 0 minus 1. Remember the 0 came from our initial position given to us in the problem. That won't always be 0, but in this case it was. So x of 8, let's go 3 there, I'll get to 8, is equal to -1. And so in my x graph, we know that particle p is starting here at -1. And now I have to figure out which way it's moving, so I can determine whether it's moving toward the origin or away. Well, again, we're looking at 8, so I want to figure out what is the velocity of particle p at time 8. Well, we were given a velocity graph, and so if we look at time 8, this is time versus velocity right here. So we're looking at right there, the value is 1, right? And if we're given a graph of velocity, all we're trying to do is come up with the actual value. I'm not interested in the slope of that line. If we were thinking about the slope of this line, now we're talking about the derivative of the graph, which would be giving us acceleration. But since we're asking for velocity, and we're given velocity, the y coordinate is 1, so v of 8 is 1. That tells me velocity is positive, which means my particle is moving to the right. And in this case, since we're starting to the left of the origin and moving right, particle p is moving toward the origin. So particle p, we can say, is moving toward the origin, and then we already discovered that particle q is moving away from the origin. So particle p is moving toward the origin, and we're going to say at t equals 8 because that will always be true. This is just for the time that we computed right now. And then particle q is moving away from the origin. I'm running out of space here, so I'm going to go ahead and try to abbreviate a little bit. Moving away from the origin at time t equals 8. So this is going to be a really good introduction to what we're going to be talking about here for the rest of the lesson, because we're going to take a lot of these ideas of particle motion that you covered. Now, you may have understood or heard we're talking about things that are covered or not covered on this year's exam. We know that for this specific exam, for AP, for students that are in Calc AP, the particle motion topics will be included on the exam through derivatives. So taking derivatives, the things that we're doing here, except for the position part, that will be on the AP exam. But for Calc PC, all of the particle motion from Unit 8 and earlier, including integration along the x-axis to the y-axis, everything that we did on here will be on this year's exam. So this will be a really good experience and practice for what you're going to see this year. So let's take a little quick overview of what we're going to be doing here for the next 25 minutes as we finish this lesson. So every time that Tony and I give a lesson, you're going to see a little diagram like this. It's going to share a couple of things. Number one, it's going to tell you what we're doing today after we follow up with the warm-up. What you should already know, meaning these are the things that we need to know in order to do this lesson. They could be things from earlier this year, or they could be things from previous courses. Typically, on this what you should know part, those are the things that Tony and I are going to continue to kind of embed and review as well. So that way, if you're not completely familiar with them, you're getting kind of a built-in AP prep review during the lessons as well. And then what you'll be able to do, meaning this is what we're going to focus on this lesson. So at the end of the lesson, this is a sample kind of problem that you should be able to understand and solve if you're following along with the problems with us. So today we're looking at topic 9.1, which in the AP's curriculum is called defining and differentiating parametric equations. So this is one of those topics that for this year only is not going to be on the AP exam. But again, like I mentioned before, even though it's not going to be tested, all the things that you're going to do in it are tested. And so just like the warm-up, it's a really good chance to review those previous topics as well as see an important topic that when you go on to the next course, you go to college, your future professors will expect you to have seen and learned. So what should you know? Well, we should know how to differentiate a function taking derivatives. We should know how to connect position, velocity, and acceleration by taking different derivatives. And we should know how to find the slope of a tangent line as well as write an equation of a tangent line. So how are our questions today going to look different than what we did on the warm-up and what you did earlier in the year? Well, here's a little example that I wrote up. That says the particle is moving along a curve at time t and has position x of t, y of t. The graph of x of t is given below, and we also know the equation for y of t to be sine of t. Find the slope of the line tangent to the path of the curve at t equals 1. So really the big idea question today is going to be how can we find the slope of a line tangent to a curve in parametric form? So we're going to start building on that. And as we build on that, like I said, we're going to be reviewing a lot of previous content. So let's go ahead and jump into it. All the problems that we see on here, just so you know, at least for today and most lessons, are going to be new and unique problems that you haven't seen before. So I'm going to make sure that we create good problems that are not just rich and rigorous in content, but also the kind of problems that you might come to see on a normal AP exam. Tony and I have nothing to do with the writing of the AP exam. We have no insights on the AP exam in terms of what it's going to look like, but we do have a lot of teaching experience, and we've seen a lot of problems, and we've written a lot of problems for our own students, and so we want to give you opportunity to engage problems in different, unique ways to fully prepare you for the AP exam. So let's take a look at this. So parametric motion allows us to extend our understanding of particle motion along an axis. So in the warm-up, particle P was moving just along the x-axis, and particle Q was moving just along the y-axis, and that's what we learned about in Calc AB, is just one particle moving back and forth along an axis. Parametric motion allows us to extend those ideas, extend those concepts into a plane, what we call rectilinear motion. So now it's not bounded by just moving along an axis. It can move sort of freely in an x-y coordinate plane. So in order to do this, we're going to have to involve 3 variables instead of 2. And the third variable, we're going to call that a parameter. Typically, at least in this lesson, is going to be t as our parameter. So think about the following scenarios. Might kind of give you an idea of how these parametrics work. And hopefully in your pre-calculus classes, you got some exposure to parametric equations, kind of see how they work. If you haven't seen parametrics or you didn't learn those in pre-calculus, it's not a big deal because very fortunately for us, parametrics are really intuitive because how you really think about things in real world time anyway. So imagine a ball is kicked from the ground at a 30-degree angle. I've got a little picture here. The scale is different, and it's not counting by the same scale. That's why it doesn't look like a 30-degree angle. But it's a 30-degree angle with an initial velocity of 20 meters per second. The ball travels along a roughly parabolic path that's modeled by the equation in the graph below. You notice that we're using a gravitational constant of -10 meters per second squared. That might bother some of us because it's not as precise, but if you're in AP Physics 1, you're probably familiar with using that rounded number for the calculations because it's still decently accurate and it lets the calculations become much simpler. So this equation, based on this information, you're not going to have to know how to come up with the equation, but the equation is going to be y equals negative x squared over 60 plus x over the square root of 3. That would be the equation that models this situation using our kinematic equations from physics. So the equation above is great because it tells us, where the ball is located, right? I know the x coordinate, I know the y coordinate, I know how far the ball is traveled horizontally, and I can tell you how high the ball is, or how high it is. I can tell you the 2 times or the 2 locations where it's at height. Unfortunately, this equation does not tell us when the ball is at each location, which is pretty important. So using parameters, we can convert this equation, and the AP exam does make you convert equations like this from rectangular to parametric form. So I'm not going to worry about that right now. It's a pre-calculus type concept, but if you're interested, there's some really good Khan Academy videos that will show you how to convert from parametric form to what we would call rectangular form and vice versa. But in this situation, the parameters would be x of t is 10t radical 3, and y of t is negative 5t squared plus 10t. So this 2 equations that we're given now tells us I can figure out the x location, how far the ball is traveled horizontally, based only on time, and I can figure out how high the ball is based only on time. So if I knew it's been in the air for 1 second, I can tell you how high it was. I don't have to know the x coordinate to do that. Whereas in the rectangular coordinate, we would have to know the x values to compute the y values. So there's a lot of advantages to doing things in parametric form. So let's look a little bit more closely at this problem. These are the same 2 equations that I have for that problem, but the only difference is now I've kind of gotten rid of the graph. But the x value, the x position is given by that same equation, and the y position is also there. And it says the functions above really allows, I'm going to put this in quotes, to separate the motion equations into x and y components. We can really think about the x location and the y location, the x position and the y position separately, but also we can analyze or group them back together depending on the situation and what we want to know. Because we know that if we kick a ball in the air in a kind of parabolic path, it's really doing 2 things. It's moving horizontally, and you can imagine how that would look by looking at the shadow that it casts on the ground, right? Looking at the shadow of the ball, the shadow is only moving horizontally on the x-axis, but it's also moving vertically up and down. So we can separate those 2 equations and realize that these things are doing kind of 2 separate ideas, but grouped together gives us a full picture of the whole motion of the ball. So using example 1, let's consider the equation above. Let's describe the motion of the ball. When I say describe the motion, I'm going to actually add a little word there. It's because let's describe the direction of motion. That's what I mean by describing the motion. Let's describe the direction of motion of the ball, meaning which way is it moving? Well, we knew that when we were learning earlier topics. The velocity would tell us that, right? If I want to know the direction something's moving, find the velocity. If it's moving on the x-axis, the velocity will tell us whether it's moving left or right. And if it's moving along the y-axis, the velocity will moving up or down. Well, since we're doing parametrics, it's kind of doing both. So we're going to look at these 2 things disjointly. So if I want to figure out the direction of motion in the x direction, let's start with that way first. I really have to figure out the velocity in the x direction, and the velocity is going to be the derivative of the position, right? So I have to take x's derivative, and notice we have 10t radical 3. So here's a little bit of a good derivative practice. I've always found that with my own students, sometimes the simplest derivatives are the ones that cause the most confusion because they overthink them. This question looks a little bit different, and students sometimes try to do the product rule or some kind of square root ideas. Remember, we can rewrite this really as 10 radical 3 times t. What the same thing is, we typically put the t in front of the radical. That way there's no confusion of whether the t is underneath the radical or not. This is more of a way to clarify what we're trying to say. But 10 radical 3 is just a constant. It's just a single number. So a number times t, when I'm taking the derivative, is just going to be the constant, right? So we know that the derivative of 10 radical 3 times t is just 10 radical 3. So the velocity in the x direction is 10 radical 3. And then doing the same thing for the y. If I want to find the velocity in the y direction, we're going to go ahead and differentiate the position of y, and we're going to get negative 10t plus 10. And we want to find specifically the direction of motion at the time t equals 1.5, right? So I got to plug in 1.5 for t for both of these. Well, for x, there's no reason to because the velocity is just 10 radical 3. No matter what's happening, it doesn't change. So our velocity in the x direction at time 1.5 is just going to be 10 radical 3. And we know that's a positive number, right? So that's that in the x direction at least, the particle's moving toward the right. Now in the y direction, if we figure out the velocity at time 1.5, we can plug 1.5 into here, and we get negative 10 times 1.5 plus 10. That gives me negative 5, if I simplify that, which is less than 0. So in the y direction, which is up and down, the velocity is negative, which means it's moving down. So the overall direction is going to be this particle at t equals 1.5. This particle or this ball in this situation is moving down because of the y and to the right. So the motion is going to be down and to the right. Now I want to jump back to that previous slide where you can see the picture of this, because this slide right here, this is the x and y rectangular coordinates. You can't see time in this picture here because it was the x and y equation. However, we just said that we knew that at time 1.5, the ball is moving down and toward the right. Well, if you imagine this ball, right, moving along this path like this, well, it's moving down and toward the right. We know that at time 1.5, we're somewhere in this vicinity right here. This is the location where the ball is moving down. And of course, because the problem is this ball is always moving toward the right. But somewhere in here is where we have t equals 1.5. So let's try a couple more, see if we can get our minds around these concepts, right? We're connecting things that you know from earlier in the course with some new ideas with the parametrics. I hope you're realizing that in parametric motion, everything is the same. The concepts are the same. The idea of position, velocity, acceleration, total distance, all those things are the same, except for now we have components that we can act on individually to give us a better picture. So one of the things I mentioned earlier is that the exam is going to not just test you on concepts, they're going to test you on skills, and they're going to test you on mathematical practices. And so one of those skills that you'll see embedded in questions is that you understand these ideas through different representations, meaning sometimes students know how to work with equations. So I give you an equation, you can take a derivative, you can set it equal to 0, you can solve it, you can get an answer. But that really good conceptual understanding of what's happening in calculus, you have to also connect that to what do those same ideas look like through a table? What do those same ideas look like if I'm only given a graph? How do those ideas look if I'm given an equation or a graph of x of t or x prime of t or x double prime of t? So there's all kinds of connections that you're making depending on that beginning information. If you've ever looked at previous AP exams or exam problems, you'll notice you get a very good selection variety of what stimulus or what kind of prompt they give you. They give you graphs, some tables, some equations. Sometimes you give an f or f prime or f double prime. And putting all those things together is really going to be indicative of a student that has mastered the material beyond just computation. So example 2 is a good example we can look at that because now we have a graph, and not only do we have a graph, but the graph of f prime, right? Remember we have position, which is x, and then x prime, which would be considered the velocity, right, of x. I should probably not prime stand for velocity. The position is just going to be the velocity in the x direction, and then x double prime is going to be the velocity's derivative, which happens to be the acceleration, right? The same connections we made before in AP type topics are going to be still through here. So now we're given a velocity graph of x, and we have this idea that we have the position of the particle moving is given by x, y. So instead of just simply calling a coordinate x comma y like we do in rectangular coordinates, it's x of t and y of t because the t value is going to be what helps us to understand what those individual points are. And we're given an equation for y of t, and the graph of x of t is above, and it consists of 3 line segments. So we want to find the acceleration vector. So obviously that word vector might be new to you if you haven't done parametrics before pre-calculus or even this year. When we write our coordinates x comma y, this is just an ordered pair. But when you're doing things in parametrics or other non-coordinate form, we can call those coordinates vectors because they're dependent upon time and they're not just a single scalar product. They have a magnitude and a direction. So it's not going to change in the math we do. It's just sort of the underlying ideas behind it that allow us to do to extend the things that we learned in Calc A, B to Calc B, C. So we want to find the acceleration vector at time t equals 3. Well, to do that, we should first find the acceleration. So let's start with the x acceleration. So we know that the acceleration in the x direction at time 3, well, based on what we wrote up here, we know that's going to be the derivative of x's velocity at time 3. Well, luckily for us, we're given a graph of x prime. Remember, we already mentioned that x prime is the velocity. So if I want to figure out what acceleration is at 3, I have to look at the derivative of velocity at 3, which is the slope of this graph. That's the connection that we have to make for the AP exam, is that when you're taking a derivative with a graph, we're thinking about the slope of the graph at that point. And so at t equals 3, this is our time. This is going to be our velocity. At time 3, we're right here on the graph. And I'm not interested in the velocity itself. I'm interested in the acceleration, which is the derivative of this graph, right? So the slope of this graph, luckily for us, at this point is part of a linear segment. And so the derivative will be the slope of that from endpoint to endpoint. You don't have to try to figure out the slope right at this point. Sometimes my students earlier in the year, when we have a derivative of a graph where it's in the middle of the segment, they're trying to figure out the slope right there by connecting from that point. This is part of a linear function. And so the slope slope of the derivative never changes no matter where you are, and the average rate of change in this case is always equal to the instantaneous rate of change. Meaning, if I pick in 2 points on this line segment and find the slope between those 2 points, that will be the derivative of every point on the graph. And so in this case, the slope of this line, we can clearly see this going down 3 and over 2, so we get a negative 3 halves slope. So our acceleration at time 3 in the x direction is negative 3 halves, and then we also have the same thing in the y direction. The difference here is we're not given a graph of y, we're given an equation for y, and this is not y prime, it's just y of t. So we're going to find the acceleration. We're going to have to move down this sort of ladder 2 derivatives, right? To go from position to acceleration, we need to take 2 derivatives. So start by finding y prime, that would be the velocity in terms of y. And so we have a derivative of an exponential function. And you remember the derivative rules for exponentials means e to the u, right? I'm taking a derivative will stay the same, but then we have to multiply by chain rule by the derivative of the exponent. So in this case, 2e to the 3t. The derivative is going to stay 2e to the 3t. But by chain rule, I have to multiply by the derivative of 3t, which is just 3, which gives me, if I simplify this, a velocity of 6e to the 3t. And I don't want the velocity. We're trying to find acceleration, so keeping your organized is going to be really helpful. And so the acceleration in the y direction is going to be the velocity's derivative now. And same rule applies. We're going to have 6e to the 3t times 3 again using chain rule, or simplify that to 18. Oops, I lost my slide there for a moment. It didn't seem to like that. I think somehow I deleted my slide. That was fun. There we go. 18e to the 3t. One of the exciting things about doing these live sessions is there's no planning for the unexpected. So something goes wrong, you get to watch it live, and we can't plan for it. We can't edit it out later. So hopefully that won't happen very much this week. So here's my acceleration vector, and at time 3, acceleration at time 3, this plugs 3 into our equation, and we're going to get 18e to the 9th power, which means our acceleration vector, the x component was negative 3 halves, and the y component was going to be 18e to the 9th power, like that. It looks like we're using parentheses. Sometimes it looks like you're calling that an ordered pair. With vectors, we can use parentheses notation, and sometimes you'll even see that with these like sort of pointy brackets. And these pointy brackets are pretty common because the pointy brackets are a good way for us to clarify that we're dealing with parametrics and vectors and not dealing with ordered pairs. So typically you use parentheses as long as you understand the context and there's no ambiguity of what you're trying to discuss. But you might also see or use those kind of pointy brackets to be more clear that we're talking about parametrics and vectors. So I'm going to skip example 3 for right now so we can get through a couple more problems that might help you as you move on and get ready to do the AP practice. But on that link underneath the video of resources, there's a nice document that you can download or print off. It has all these problems and all the notes there, and that probably in there. And then the next day, you should have the typed up solutions to all these. So if you want to go back and try example 3, you can, and you'll see the solutions in there to see if you did it correctly. The last thing I want to mention today, which is kind of a big important idea of topic 9.1, is this idea of a derivative, right? And that we know we're interested in finding things like dy dx, right? The derivative of y with respect to x. And so we have these parametric equations, but in general, even though we're doing parametric equations, we're involving time. We put them together. The graphs that we're graphing are still going to be in an xy plane. And so because they're in an xy plane, we're always interested in this idea of a tangent line, right? And we know that the tangent line of any graph in the xy plane has a slope of dy over dx, right? dy over dx is going to give us the slope of that tangent line. That doesn't change just because we're in parametrics or polars. The second half of Unit 9 is going to involve polar equations and polar graphs, and extending those ideas that you learned earlier in the year to polar functions. And even with polar functions, we'll discuss this idea of tangent lines to a curve. The tangent line to a curve, whether you're in rectangular coordinates, whether you're in parametrics like today, or whether you're in polar coordinates, the tangent line will always have a slope of dy over dx. So we have to figure out how we can do that. And so we know that dy over dx is going to be equal to dy over dt over dx over dt, and that should make some logical sense, right? Because we know dy over dx. If we think about this as dy over dt over dx over dt, then we can multiply by the reciprocal of this and call that dx or dt over dx, and that will reduce to dy over dx, right? So we can see how dy over dt over dx over dt, the ratio of those two quantities will give us dy over dx, which will be the slope of the tangent line. So whenever you see the phrase find the slope of the line tangent, immediately you should realize tangent line slope is always going to be dy over dx. And we got to figure out how we compute that. Well, for a parametric form, we compute that by finding dy over dt and then finding dx over dt. So in this example right here, they were kind enough just to go ahead and give us those values, right? Dx dt is given by this, and dy dt is given by this, and to find the slope of the tangent line, which is dy over dx, we just have to figure out dy over dt over dx over dt at time equals 4. So if I plug in 4 into these equations, dy on top, that's going to give me at t equals 4, the natural log of 5 over plug in 4 to the second equation, you're going to get 4 squared minus 3, which is 13. So we know the slope of the tangent line for these parametric equations is going to be simply whatever the natural log of 5 over 13 is. So that idea is going to be a nice, pretty important topic. And if you think about some questions that we can ask with this, right? So I'm going to show you a quick problem here that we're not going to have a chance to do together. Again, I would encourage you to kind of try it. I want to kind of mention how you might tackle this problem here. So a particle moves along a curve in the xy plane such that its position, right, we're talking about parametrics, x of t and y of t, is given by the equations 1/3 t squared or tq minus 2, and then y of t is going to be 3t squared minus 4t plus 1. The question is going to be find all the times where the line tangent to the path of the particle has a slope of 2. And so I want to at least begin to set this up for you, so that way when we get done here in the next minute or two, you'll have a chance to back and see if you can finish this problem out. But I want to show you how you might set this problem up to begin to solve it. Because again, look at the key words in the question. Sometimes we get so overwhelmed by the upfront information that we get overwhelmed by that and start focusing on this instead of really focusing on what they're asking, right? So the question is, we're talking about when the line tangent to the path of the particle. We know that the line tangent, the slope of that is the same thing as saying dy over dx. So what they're asking is, when is dy dx equal to 2? We also know that we have a way to find dy over dx, right? Dy over dx is going to be dy over dt over dx over dt. And so if we found dy over dt and dx over dt, we can just plug those in, and we're given an equation for y. So if I want to find dy over dt, that's just the derivative of y with respect to t. So in this case, this derivative becomes 6t minus 4. And then similarly, if I want to find dx dt, I'm taking the derivative of x with respect to t, and this derivative just becomes nice and clean as t squared. So to solve this problem, I know that dy over dx, which is supposed to equal 2, can also be found by taking dy dt over dx dt, which means the 6t minus 4 by dy dt over dx dt, which is t squared, should be equal to 2. And this is going to be the equation that we want to solve. If we can solve this algebraic equation, now we're going to be able to figure out what those t values are, find all the times t to do that. I'm going to put off here to the side. If you do solve this, the solutions would end up being 1 and 2. So maybe you can kind of go back and see if you finish solving that one. How would you solve the algebra? I always found that sometimes it's interesting because sometimes my students will do such a great job with the calculus, and then the algebra at the end is what trips them up. So it's always important not just to practice the calculus ideas and skills, but also those algebra skills that we're not losing points because the algebra misunderstands. So at the end of the lesson, let's take a look and debrief and summarize a little bit. And enduring understanding is something that hopefully these little topics will build up and work together to help you have a better concept of how calculus works. And so here we're kind of getting the understanding that derivatives can allow us to solve real world problems involving rates. And a couple of key takeaways that I hope that you'll remember moving forward is that the slope of a tangent line in parametric form is given by this equation. And then also the concepts of motion in 1D. That means moving along the x-axis or moving along the y-axis. Just those basic motion problems. Those same exact concepts and ideas can be extended to 2 dimensions or parametric forms. A couple of common errors, and Tony and I will continue to have each lesson some things to kind of remember or look out for. These are actually errors or things that you should remember. If you don't, the mistake of these are what would cause the error. To always consider both components of a function. Meaning that example we did to describe the motion of the particle. Sometimes students only look at the x direction or the y direction and say things like it's moving to the right or it's moving down, instead of realizing these are both together and the particle's moving down and to the right simultaneously. And then the slope of a tangent line is always dy over dx. Even if you're in parametrics, even if we're in polar form, the tangent line to a curve is the rise over the run, which is going to be the change in y over the change in x, which is dy over dx. And also be really careful when you're solving problems. Sometimes they give you an equation or a graph or a table of x of t or y of t, and sometimes they give you x prime or y prime, which is the velocity. You really have to pay attention to which equation you're given and what to do with that equation. So at the end of every lesson, we're going to have an AP exam practice practice problem. You're not going to need to solve it right now, but what's going to happen is the warm up for tomorrow, the warm up for the next lesson will always start off with the same problem. So I'm going to put the problem on the board, and if you don't have the files or you haven't downloaded them or you can't download them, print it out, maybe get your phone out and take a picture of the screen and see if you can find some time before the next video to try these problems. It's one step with part A, B, and C that's going to really tie together the things that we talked about today, as well as a lot of those previous ideas and concepts that are embedded in today's lesson that will be on the exam come springtime. So take a little picture of this, and then tomorrow at 9 a.m. time live, Tony Record will start with this problem, kind of walking you through it line by line and making sure that you're on the right track. But it really is going to be important that you begin your journey toward the AP exam to try these problems when you get a chance. So hopefully I'll give you a couple seconds to take a picture of this, and then we will look at the last slide here in a second. You'll notice on this problem there's a lot of things going on. We have a graph of x of t, we have an equation of y of t, so we're connecting those representations, and a part of the graph of x of t is this parabola shape here on the right, and in the stem they give us an equation for that parabola. We're going to be finding the velocity vector. We're going to be talking about the equation of the line tangent. We're going to see if we can extend the idea of how do you write a tangent line. It doesn't change just because we are in parametric form. And then talking specifically about the horizontal movement. Is it moving left or right at time 7? So think about those problems. Think about how we learn some things, what you understand about them, how you might tackle these problems that maybe you haven't seen before. This brings us to the very end of our very first lesson. Thank you guys for being our guinea pigs today. This was the first of 28 consecutive days of the week, Monday through Friday. We'll be doing these live lessons. Don't forget these will be recorded and uploaded to the YouTube channel shortly after the videos are done, so you can come back and watch them later. And don't forget the full complete schedule. The college board released for 34, I believe, 30 or so of your AP exams. We're going to have these opportunities for you to join live or watch the recorded lessons with different AP teachers around the country. So thank you so much for joining us today. Don't forget we'll be on here tomorrow. I hope that you will join us again each and every day. Tomorrow morning, Tony Record will be giving the lesson, and then you will see us kind of bounce back and forth each day between the two lessons. So have a great day. Make this a great day. Get a little bit better every day as you prepare for the AP exam, and take care of yourself. We'll see you soon.
Hello and good morning to everyone that's joining us live, and certainly welcome to those of you that are watching us on demand. We're so grateful that you're able to hang around with us and take a look at topic 9.3, finding arc lengths of curves given by parametric equations, parametric functions. Just a quick reminder that it's not too late to access the documents that appear with today's lessons. If you click in the link down below in the description, it'll guide you to a location where you can download and even print if you prefer that particular document. We're going to be solving a few free response questions today, so having that in front of you could certainly be helpful. And you can take care of that while I do a few housekeeping items before today's stream. Once again, my name is Tony Record. I'm a calculus teacher at Avon High School in Avon, Indiana, just west of Indianapolis. And I'm sure I speak for my BC calculus partner in crime, Ryan Passwater, when I say that we're absolutely overwhelmed by the tremendous amount of support that both community teachers and even students that have shown us already in early stages of these virtual lessons. We just want to remind you that we're going to be here for you every day from now until May 1st to discuss some new topics that perhaps maybe you didn't have quite enough time to cover when you were in your physical classrooms. But we're definitely going to try to take those ideas and tie them to older ideas, ideas that will likely be tested on this particular AP exam in May. So take a look at some of the upcoming lessons. I know there's been some questions about what's coming up ahead. But obviously today we've got the arc length parametric. Brian's going to come back on tomorrow, Friday the 27th, with some solving motion problems using parametrics and vector value functions. And if you just take a quick glance at the week ahead, you can see that we're going to transition to Unit 10. Unit 10 is all about the wonderful world of series convergence, and then moves on into Taylor polynomials. So for the most part, next week's it's going to predominantly revolve around series convergence. Each of those are Monday, Tuesday, Wednesday, Thursday, Friday in order. And the three topics that have the stars by them are the three that will certainly be tested on the AP exam in 2020. So we'll definitely put some special emphasis on those. Like I said, we're working hard to make sure that we tie all of these new topics into the old ones so that you're going to be more comfortable in AP exam time. And I think Brian did a really good job of that yesterday. No matter what the subject is, all of your virtual instructors that you guys have, we want you to do well. We want you to earn the highest possible score that you can on your advanced placement exam. Some people willing to bet that your own classroom teachers feel probably the same way. So just as we're here for you students, we're also here for your teachers. We know that you might live in a district where you have a lot of challenges to your e-learning experience. Maybe you have a limited number of days that you're allowed to have virtual instruction. Maybe your virtual instruction mechanism is for the moment non-existent. We think this is going to be a great place for you guys to come and get instruction in sport. And for those of you that might be fortunate enough to be or unfortunate enough in a 5-day-a-week virtual e-learning environment, we think that we can still provide you with instruction that can complement what your teachers are doing. So in any event, this is certainly unusual circumstances with the advanced placement test this year, and to say the least, but we can certainly overcome this. Calculus isn't going to go away. So let's go ahead and get to it here. So we got a warm up today that actually was supposed to be your homework assignment, right? We know that you all did this homework assignment. I'm going to go ahead and call that problem up. It also appears as the very first problem in your documentation. And if you remember, the stem of this problem said that for time greater than or equal to 0, particle is moving along the curve so that its position at time t is x of t, y of t, where y of t is 4 sine quantity t squared minus 1 plus 3. The graph above contains a portion of x of t which consists of two line segments. A quadratic function defined by x of t is 1/2 t minus 8 squared plus 2 for t is between 6 and 10 inclusive. So you're asked three separate questions here. And what I want you to do is, I don't want to give a large amount of time for those of you who have not taken a look at this problem. But tell you what, let's just set the timer for 1 minute to have you take a look at this. And if you had a chance to look at it, maybe you can kind of reread some of your parts, check some of your work. And if you didn't get a chance to look at this, maybe you can start to develop some strategies to set up at least 1 or 2 of the parts. About 20 seconds. All right. So if you're new to this problem, by no means did we expect you to get a solution to that in just 1 minute. But hopefully you got a chance to kind of think about some of the things that were asked. And let's check and see how you guys did. So for part A, we're asked to find the velocity vector of the particle at time t equal 9. So we have to think back to, okay, well, how do you find velocity when you're given these equations? And well, we come up with the idea that we take the derivative of position. So we're going to do that. So we're going to take x prime of t. And then when we do this, we have to be kind of clever about this. We have to think, okay, well, this x of t is very much all over the place. We've got x of t defined as this diagonal line for a while, and then it changes its mind as this horizontal line, which of course we have equations for. And then we have this parabola shape, which is really what's going to be defined down here in this expression. So when t is equal to 9, we notice that that's certainly along this particular interval. So this is the x of t that we want to take the derivative of. And it's a pretty easy derivative. The 2 times the 1/2, of course, cancel. You'd have t minus to the first, no chain rule needed, and the derivative of 2 is 0. So there's our x prime of t. We do the same thing for y prime. This derivative might be a little bit tougher, but nothing that we can't handle. The derivative of 4 sine of an expression would be 4 times the cosine of that same expression. Notice we have the chain rule coming up here. So the derivative of t squared minus 1 would be 2 times t, and then we finish it off with a derivative of 3 is 0. So now that we've got our two general derivatives, we can specify exactly what our velocity is going to be at this particular moment. So we're just going to plug 9 in for our t. So x prime of 9 is 9 minus 8, which is 1, and y prime of 9 is going to be, we're going to think about this one a little bit. 2 times 9 is 18 times 4, that would be 72. And then we have the cosine of 9 squared minus 1, which is 80. It's kind of a hot mess, but honestly, without the use of the calculator, there's nothing that we can really do with that. So I'm going to show you a little bit about what this value is here in a moment. But that would take care of our two values for our vector velocity. But we want to present this in a little bit better way, I think, because it did ask to find a velocity vector. So probably the best way, maybe the most popular way, is to present it using these, we call them angle brackets. I've sometimes heard them referred to as vector brackets. They seem to kind of coincide with vectors quite a bit. And that's probably the strongest way to interpret this. Now, if a student were to have used parentheses here, we're not the ultimate fans of it because it can be a little bit lost in terms of its context. But given the fact that you were told that this is a velocity vector, we probably look the other way if you had the parentheses. I know in linear algebra courses a lot, they'll express vectors as such. And for those of you who might be dabbling in AP physics, the IJ notation is accepted on the AP exam, but it's on the AP Calc exam, but it's never ever going to be here. All right, so there's our part A. Let's take a look at part B now. Part B asks to find the equation of the line tangent to the path of the particle particle at time t equal 1. Well, the very first thing that you want to read through here is find the equation of the line tangent. It's very likely if you're a BC student, you have probably found equations of tangent lines many times over. So you know that the main tool that you're going to use is perhaps the point slope formula, which looks a little something like this. It's possible maybe you like to use the slope intercept formula. They're both workable. I teach at a school that has a very large enrollment of calculus students. We have about 300 students in our Calc program, and they're coming in from all different kinds of Algebra 1 backgrounds, and I have a lot of students that like to use the slope intercept. I'm going to go ahead and use the point slope formula for the solution to this problem, however. And one of the things I want to point out is that if you look through this equation very carefully, at no point, at no time, at no instance do you see the letter t. So we don't want to plug 1 anywhere into this particular point slope formula because there's no place for it. So we have to think about, oh, okay, well, we want an x value and a y value, right? The specific x sub 0 and a y sub 0. And we're going to find those when time is 1. So the very first thing that we can do is think about that. So I'm going to find the y first. So the y value at time 1. We go back up here to our y equation here, and we replace the t with 1. And oh, it's nice that we have 4 sine of 0, which of course is going to be 0, and we add 3, and there's our y1 value. And then we do the same thing for x. But here's where you got to be really careful. Be interesting to see for those of you that have worked this problem, say the night before, where you went with this problem. Oops, that's not 3. So if we take a look at this x of 1. Well, it's really tempting to want to right back here and evaluate this x of t expression when t is 1. After all, we just did it a moment ago, right, in part A, when we evaluated at 9. But we have to remember that this particular expression is only valid between t being 6 and 10 inclusively. So we have to think about, okay, well, what is the x when t is 1, and enter the graph again, right? So at t equal 1, we find that the x value is going to have a y coordinate here 2. That is what we want to use for our x of 1. So it's a very tricky problem. All right, we've got our y sub 0 and our x sub 0. It would certainly be nice if we had a slope, right? Calculus is sort of kind of dependent upon slope quite a bit. We use it quite often. So what we're going to do here is take the slope and know that the slope is just really the derivative of y with respect to x. It's the change in y over the change in x. It's an idea that's embedded into the Cartesian, right? The rectangular coordinate plane, x-axis, y-axis. Parametric equations kind of have a little bit of an issue with that because of the variable t that's involved. But that's okay because in the lesson that's hopefully you took a look at yesterday with Brian, we defined that the dy dx in parametric can be written as dy over dt divided by dx over dt, right? Essentially those dt's, you think of them as sort of canceling out, I guess, and leaving behind this dy dx notation that we're looking for. And the good news is that we've already found the derivative of y, right? It's this or cosine expression. So I'm just going to rewrite that, just going to show good notation. I know some of you might be anxious to start to plug in your one. That's fine. And the dx dt, now we're in the same situation as before. We're looking at this x of t equation, and we've got to think to ourselves, what is the derivative, right? What is the derivative of this graph? How do you get the derivative of the graph? Well, it's often easy if that graph consists of straight lines, and that's why so often they do. And we just find out, oh, that's just the slope, right? The slope along here, which happens to be 2. So we have this constant down here. Okay? And then if we want to go ahead and evaluate this at 1, we can. If you want to show notation with that, there's a variety of ways to do that. You could say dy dx such that I could put the ordered pair here 2, 3. I could put that the time t equal 1. Maybe that makes the most sense. And now I'm kind of allowed to plug 1 in for that t. And let's see, when I do that, I have the cosine of 0. We know that's 1 times 4 is 4, and then multiply by 2 times 1, which is 8. So we're going to get 4 for that slope. Now you have all the ingredients to write the equation of your tangent line. So you go back to your point slope formula, and it would look something like this. Right? Moving on to part C. It asks, is the horizontal movement of the particle to the left or to the right at time t equals 7? Explain your answer. So we got to think about horizontal movement in general, moving left, moving right. It's always been tied to velocity, and we know that velocity is first derivative. Now, if we're focusing more so on the horizontal movement, then you got to think, do you really need to analyze both of these components, the x and the y? And you find that horizontal is tied solely to the x component, of course. So if we take the derivative of x and plug in 7, right, we want to figure out what's happening right at 7. Pretty much a lot of this work has been done for us because once again, we have to pay really close attention to the x because at time 7, we don't want to get kind of thinking that we're using the same area or the same portion of the x graph that we did in part B. We're back up to the portion that involves the parabolic shape. So if you recall, we've taken that derivative. I'm going to outline in part A. There's no need to rewrite that derivative. If he's already on your paper for part of this free response question, you've earned the right to use it again. So if we plug 7 in for t, it's pretty clear you get a negative 1. Right? Now, maybe that's the easy part. Now we have to explain what's going on and know what's going on. And because this derivative is negative, we can say that one way to write this is the horizontal movement is to the left in this case. Right? Derivative is negative. We're going to move left. The derivative is positive. We move to the right. And it's not a bad idea to say exactly when at time t equals 7. And let's give a good reason here. Let's say, well, the reason is because that this derivative of x at 7 is a negative number. And that would tie things up very nicely. As I was solving this problem, I kind of thought, well, maybe it'd be nice if we could really get a good look at what's really going on in this question. So I've kind of added a little technology piece that's going to talk about parts A and C. Let's look at part C first. So I'm going to leave the screen for just a moment, and I'm going to bring up it's a graphing calculator application. I'm using the TI Inspire CX2 here. By no means am I expecting you guys to understand how does the TI Inspire work as a graph. Some of you might use it. Most of you probably don't. But that's really besides the point because any kind of technology where you graph a parametric function, whether you have a TI-84 family of calculators, Desmos does a good job. They all will take care of really what I'm trying to address here. And what I want to do is I want to path plot this. Let's watch a movie. That's what we're going to watch a movie. We're going to watch the movie about this parametric function here. So I'm going to go ahead and I'm going to start this animation. And what I want you to pay close attention to is the time here. And notice I'm focusing on the time when t is 6. And if you're wondering, well, what is this parametric equation? Well, basically, I return back just real quickly, knowing that I'm going to define this only between 6 and 10, I am pairing up these two guys. Right? So those are the two things that I actually entered into my fields for my x and y for parametric. So if I watch this, grab some popcorn, this is riveting. Let's take a look. What's going to happen when we get to time equals 7? This particle is kind of oscillating up and down, but it is moving to the left for the most part, getting pretty close to 7. I'm excited. I know you are. And all of a sudden we see at 7, we continue to move to the left. It's continuing to move that way. And it's kind of starting to change its mind maybe a little bit. It's starting to sort of compress a little bit. And if you think about part A, which was dealing with time equal 9, let's see what happens at time equal 9, which is coming up. First of all, at time 8 or around there, it seems like this guy's decided he's going to turn back and go the other direction. So that's interesting. If you were to plug a number larger than 8, you may get a positive derivative. Now, at time 9, that was part A. That was the velocity vector. Let's see what happens here. It's coming up, and right there's time 9, and then we kind of miss it. It's kind of disappointing, isn't it? And if this thing were to continue, I'm going to stop the animation because I know the ending of the movie and I'll spoil it for you. This particular dot is just going to end right around in here. Okay? But what I wanted to do is show you something a little bit more specific about what happened at time 9. So I was able to take a really quick, high-resolution, high-speed camera screenshot, and right here it is. Super duper high-speed camera action shot of what is happening at t equal 9. I would have shown this to you live, but this only took 13 takes to take care of. So here's where the point of the particle would be at time 9. Now, over to the right, I've got a notes page that just shares some calculations that we've already done. We noticed that the position of the particle, the x position at time 9 was 2.5. That looks about right. The particle somewhere between 2 and 3. And it looks like the y position was whatever 4 times the sine of 80 plus 3 is, which is negative 0.9. So pretty close to negative 1. But what I'm concerned about is that answer to part A, that velocity vector. So we see that the derivative of x at 9 is 1. So that would be sort of our x component of that velocity vector. So maybe it would look a little something like this. Extending from that point, we would go 1 unit to the right. Since this is positive, we would go to the right. And then if we look at the y component of that vector, that velocity vector, that 72 cosine of 8, remember that one that we found? If we convert that to a decimal, let's just say it's pretty close to negative 8. So that means from that point, there's this sort of force that's wanting to pull us down about negative 8 in that direction, which if we start here at negative 1, I don't have the scale finished here, but that'd be about negative 9 or pretty close. close. Let's say it's approximately 9. And then really what all this means is that, you could think about the tip-to-tail method for developing vectors, and you could actually put, your box in place here. And then what this vector is really doing is it's moving to this opposite corner right there, right? So if you add that x component to that y component, you have this purple value. And if you want to think about this more in like a real world context, let's say that this was some amusement park ride. That'd be kind of fun, right? You have to ride an amusement park ride that did that. And by the time that point got to here, it's like the forces on your body are going to want to send you the direction of that purple line. And the longer that line or that ray is, the faster you're going to go. Okay? But unfortunately, this ride's going to send you back this way, so you're going to experience that sort of jerk reaction, and that's what makes rides fun. Now, all of this is not something you need to know for the advanced placement test. I wanted you guys to see a little bit bigger picture about visually what does this vector function look like and how does it act in the real world. This is certainly more along the lines of something that you can maybe physicals. Right? All right, let's go ahead and move on to our lesson overview, getting into some of the new stuff today. And what we are going to do today is we're going to find lengths of curves defined by parametric equations. That's our main goal. And we're going to discuss the concept of speed as it pertains to parametric equations. Now, the things that you should already know. Well, we should already be pretty confident about being able to differentiate a function. We've actually done that before in our warm-up. Integrating expression is going to be really important in this lesson. And we certainly need to know how to evaluate a definite angle. The arc length formula in rectangular is something that you have to be familiar with as well. That's going to be a springboard to our arc length in parametric. The arc length formula in rectangular, it was topic 8.13, which may or may not mean anything to you if you don't follow the exact order of the new course exam description, unit 8, topic 13. But it's likely it's something that you have been taught perhaps maybe shortly before your schools may close. So what we're going to be able to do here is basically take a smooth curve C that's represented by some parametric equations. Maybe we're going to be given some interval, and then we're going to ask, hey, what is the length of the curve that resides along those given values of t? And I've got a little surprise here. This particular parametric equation has a really neat graph that kind of looks like maybe upside down ribbon. And it's not a problem that we're going to actually solve today, but I would challenge you to, after we kind of go through this lesson, if you want to look back at this and maybe use technology just to kind of get a feel for what this arc length would be, because you won't be able to do this by hand, you could certainly do that. And any teacher that's watching, you could actually ask your kids ahead of time to kind of predict what the answer is going to be. I'm going to spoil the surprise a little bit. The length of this arc is about 50 points and some change, but you can kind of see that probably seems pretty reasonable given the scale that you're going to get. So you can check that out if you're interested. What we're going to check out is our first guided practice question, which is going to ask us to find the arc length of the rectangular graph of y equal quantity 2x to the 3 halves over 3 from x equals 0 to x equals 4. So do we all remember what that formula is? So I've got it coming up here in a second. So I'm going to share it with you if you've forgotten. That's okay. That's what we're here for. So we can say that this arc length formula, and we can use L, we can use S, a lot of textbooks, a lot of teachers use a lot of different things, but in the rectangular world, we're going to integrate from the given boundaries 0 to 4 of the square root of 1 plus the derivative of our function squared. So in this case, the function is denoted by y, so I'll say y prime squared. And this is going to be a function or an integral that's going to be taken in terms of x. Okay? So you see that it's pretty important that we know what the derivative of y is before we can proceed. So we'll take care of that. Maybe I'll do that off to the side here. Y prime is, let's see, it's going to be a tricky derivative. That 3 halves comes in front. We still have this 1/3 denominator. And this is where this can be very tricky because the derivative of this quantity 2x to the 3 halves is going to start off as 2x to the 1 half, but we have the chain rule that we have to remember. The derivative of what's inside is 2. It's very easy to forget things like that, so have to be careful. It's nice that 2 showed up because a lot of stuff cancels, and we end up with just quantity 2x to the half, or the square root of the quantity 2x. So we're going to go ahead and take that guy, and we are going to plug him in for our y prime. And as I do that, I'm going to go ahead and square this, if this is okay with you. I'm going to go ahead and square 2x all to the 1/2 power, which should just give us 2x all to the first with respect to x. And in order to handle this, we're going to have to do a u substitution. We think through this, the u is going to be 1 plus 2x, but unfortunately his derivative produces a 2, so that's a pretty easy fix, right? Eventually, you know that there's going to be a 1/2 that's going to reside on front, and then we're essentially integrating the square root of u now. Okay? Now, since I'm committing myself to go ahead and evaluate this definite integral in terms of u, the boundaries are going to have to change to u's as well. So if I let x be 0, the lower boundary would be 1. That would be now in terms of u, and the upper boundary, I believe, would be a 9. All right. So we integrate this, and we end up with, let's see, the u sort of u is having a dream. You'd be thinking, man, just call me u to the half. I'd be so much easier to work with. So u to the half integral will be u to the 3 halves divided by 3 halves, or times 2/3, and we can keep our boundaries at 9 and 1 in terms of u. And we see that the 2's will remove themselves from the problem, and we have 1/3 times u to the 3 halves power, basically. So if we evaluate, we see that we would get 9 to the 3 halves. Well, square root of 9 is 3 cubed is 27, track, and then evaluate 1, and we have a fairly clean answer of 26/3, which I will tell you is a blessing. It's if you work with arc lengths, no matter if you're in vectors, if you're in parametric, if you're in rectangular, it's very difficult sometimes to be able to do them by hand. They have to be written very special so that you can handle the mathematics, not mostly the integration process, in order to produce an answer without having to use technology. All right, let's take a look at what's up next here. What's up next here is sort of walking you through this arc length formula that I'm going to introduce today, the new arc length. This is the arc length that's going to be associated with parametrics. And remember, you got to think parametrics deal with a y expression in terms of t and an x expression in terms of t, and we really don't have anything that has anything to do with t with our good friend here, the arc length formula for rectangle. So if I talk you through this, I'm just going to kind of basically go through this 4-step, 3-step evolution, and I want you to kind of look and see if you can tell what transpires from one step to the next. I'll give you about 10-15 seconds just to look at this first step. Maybe you don't even need that much time for this one because really all that's going on is the dy dx is being renamed as dy dt over dx dt, just like we talked about. All right. So then we go to the next step and we see, well, what's going on here? Well, it looks like we're getting a common denominator of dx over dt squared. That's one thing that we're doing. There's actually 3 things going on here. We're introducing a factor of dt in the numerator and the denominator. That might seem kind of strange, but for all intents and purposes, that's equivalent to 1. And the thing that does is it sort of gives us the potential for this to now be written in terms of t. So the boundaries are going to switch from the x values to these values a and b that are going to be innately attached to t. I'm going to show you that in the formula here a little bit. Okay? Now, at the next step, a lot of stuff begins to happen. It looks like a lot of stuff begins to happen because essentially this dx dt that's in the denominator, that's squared. If we take the square root of it, it just becomes a normal dx over dt to the first power. That will essentially cancel. I can probably show that here with that dx dt. Right? And then pretty much what you're left with is the formula for a parametric arc length that we're going to work with. And of course, it's possible if you want to use a different type of notation, the Newton notation of primes, and you could use f of t, g of t, it could be x of t, y of t, as long as they both have numbers. All right. So let's take a look at the official length of the parametric curve. Just as a curve, c is represented by parametric equations. X is f of t, y is g of t, t is between a and b, like we just spoke about. That's going to be our parameters for our t. And we know that f prime and g prime have to be continuous. C is traversed exactly once, which just means we don't want this graph to kind of overwrite itself because that could definitely throw off our result. Then we got our arc length formula in whichever form that you prefer to use. So we can go ahead and take a look at another example here. At time t, the position of a bug moving in the xy plane is given by the parametric equations x t y t, where dx dt is t, dy dt is t squared. Find the distance traveled by the bug from time 0 to time 0.8. So we start off, and distance traveled, arc length, they're synonymous. They're the same thing. It doesn't really matter what we call it. I might use d for distance here. We know that we're going to integrate using the given boundaries. Most often those boundaries are going to be given to 0 to square root of 8, and then we have the square root of, and if you remember the formula, it asks us to take the square of the dx dt and the dy dt. Unfortunately, those have already been taken for. So the derivatives, at least I should say, have been taken for. So you don't want to differentiate t and t squared here. They've already been done so. So if you just square each one, we have something that might look like that at this point with respect to t, and then we can start doing some simplification because this doesn't look like I can probably integrate this right now in this present form. But if you factor out the square root of t squared, that's your common factor, you essentially have t, right? The square root of t squared would be t, t. And we're okay to do that, knowing that we're on this interval that's for the most part positive, not negative. And the square root of 1 plus t squared is what's left inside that radical expression. Okay? And I think we have another u substitution here. Maybe I'll outline this if anybody was a little lost on the last one, but typically BC students are starting to feel pretty confident about u sub. So it looks something like that, right? And the 2t that we have here for our derivative, the fact that the t's match is a wonderful thing, but the 2 not so much a wonderful thing, but we can just offset that with a 1/2 in front. And just like before, we'll rewrite this in terms of u. And so the zero boundary is going to turn into, let's see, 1 plus 0 squared, that's 1. Square root of 8, square root of 8 squared is 8 plus 1 is 9. And then we have the square root of, well, that would be u du. And this is starting to look awfully familiar. It's like deja vu all over again. This is like deja vu all over again. All right, well, let's take a look. Let's go ahead and integrate this. 1/2 u to the 3/2 times 2/3. Yeah, this is awful familiar, isn't it? From 9 to 1. This is the exact same thing that we did a moment ago, and we ultimately got that answer 26/3 in the previous example. Maybe you can flip back and verify that if you've been following along. So what's going on here? Well, what's going on is we essentially just took the same thing. All right, we did so with the rectangular form, and we did so with the parametric form. And I think the rectangular form, if I can write it out here, it was the y equal, what was that? 2x to the 1/2 all over 3, I believe, right? We can verify. I would hate to have written the wrong thing and graph it and waste your time. That 2x all to the 3/2 over 3. So let's make sure I change that. Good thing I checked, huh? And if I bring the graphing calculator back in for just a second, I'll go to another page here. And I've actually taken the liberty to graph the parametric equations here. And I want to drag this a little out of the way and talk about something, because we would have to integrate both of these in order to produce an x of t and a y. Remember, right now these are derivatives. So if we basically solve this really simple differential equation, we would get t squared over 2, okay, plus c. And then this guy would be t cubed over 3 plus c. But you can see I'm kind of looking at the trivial case here. I'm going to consider both the constants 0, because it really doesn't matter what the vertical shift is going to be. That's not going to have an impact on our arc length per se. So we've got our sketch there, and why not? Let's go ahead and I'll go into a graph entry, and let's graph a function. Let's graph that function that was a part of that problem. It was 2x. I think I've been able to find my x, and I'm going to hate life for that. Let's see, over 3. Yeah, there we go. So you can see in orange we have essentially the same graph, because the orange is the rectangular version and the blue is just the parametric version. And even though they have obviously the different intervals, that's an important part about why these do produce the same answer. Okay? The AP exam is typically not going to have you convert from parametric to rectangular. That's definitely a pre-calculus idea, but it's nice to see how that ties back in together. All right, the last little idea I want to discuss here, the idea of speed and parametric. You recall from earlier in your learning of calculus that speed is the absolute value of velocity, right? Well, what does that look like in the parametric world? Well, if x and t and y and t are twice differential functions, then the speed at time t is defined as, and you got to look at this very carefully, because this is really a bold v, which is kind of indicating the idea that it's a vector. Other these look like absolute value symbols. They actually act more like another kind of word. We say the magnitude v of t. Sometimes in other courses you might see double brackets, right? You might see these things wrapped around, right? That's acceptable as well. But we're looking at defining that as such. We're taking just simply the square root of the sum of the squares of the two derivatives. The internet's full of wonderful proofs for this. It's just really a manifestation of Pythagorean theorem. If you look at this, you can probably see the Pythagorean theorem residing in that. So if we revisit our warm-up problem from earlier, remember that graph of x of t that just couldn't make up its mind? Well, for t greater than or equal to 0, a second particle is moving along the curve so that its position at time t is given by x of t, y of t, where x of t is given in the graph up. However, for this particle, y of t decides he wants to be kind of mischievous, and he is going to call himself x of t squared. Find the speed of the particle at time 1. All right. Well, for this particular problem, go ahead and we could use this notation that the speed here, the magnitude of velocity is, and we would say the square root of. All right. Now for dx dt, we have to take the derivative of x. We got to think about where we're going to take the derivative of x, which is at time 1 again. So we're looking at the slope one more time. So that would be a 2 that we could square, and then the dy dt is going to have us work a little bit, right? We're going to have to take that derivative. Might do that off to the side here, and he is a very unusual little guy. The derivative of x of something would be x prime of that sum, and yep, this is chain rule written all over it, right? You're going to have 2t there off to the side. So if I take all of him, wrap him in some parentheses, he's going to have to be squared as well. That's what's going on there. And we got our integral. Or, we don't need to integrate. I don't need a dt. We got our radical, our square root. So if we go ahead and simplify, we have a 4 here. It looks like we're going to have a 4t squared, and it looks like we're not going to be able to do a whole heck of a lot with this x prime of t squared for right now. All right. So I think we're at a place where we can probably evaluate this at 1. So you're just going to plug 1 for t's. And doing so, we have 4 plus 4, obviously, and x prime of 1 squared, x prime of 1, right? And again, that relates right back to that derivative, right? That derivative value, which is going to be 2, and we square it. That's going to be a 4. And by the time we simplify this, the arithmetic will give us 20. And you could leave it like that. You could simplify it into a simplest radical form as well. All right. Now we're getting kind of close on time here. I got several checks for understandings, and Brian and I are always going to be in the habit of probably more than what you can do in a simple 45-minute session with us. But okay, we want to give you guys resources. We want to give your teachers resources that they could actually, not just use this year, but they can keep for the future. And we know that you miss school. We understand. We're very empathetic to that, and we know that you miss those little homework assignments here and there. So we might have you guys practice 2 or 3 of these, and just know that the keys are always going to be available. But in this particular case, let's say a teacher gave a quiz which contained the following question: a curve C is described by the parametric equations x of t is t squared, y of t is 2e to the 2t. Set up an integral expression that will compute the length of the curve from t equals 0 to t equals natural log of 2. And we'll say that 4 students wrote each of these responses. Now let's indicate which student wrote the correct response, and let's maybe determine any errors in the other 3. All right. So if we work this together, we'll say, all right, well, the very first thing that we probably need to do is take the derivative of x, because that's part of that formula, right? And we end up with 2 times t. And let's do the same thing for the y. So it's a little bit more complicated, a little chain ruling on there. 2e to the 2t times 2, which is 4e to the 2t. Now notice each of these will have to be squared, and in doing so, it looks like it looks like Courtney and Brian didn't do real well with this problem. Brian really struggled because he forgot his square root expression, square root symbol, and Courtney just didn't take the square of 2t very well. It looks like Avery and Drake are still in it, but we're gonna have to give Drake a win here, right? Drake's got the correct setup because Avery did not square the 4e to the 2t correctly. Just probably forgot to square 4. Teachers, if you're looking, this is basically a manipulation of a multiple choice question that I'd written long ago, A, B, C, D. But knowing that this particular year's AP exam might be very likely will be free of multiple choice questions, it's a way to kind of get engaged with wrong answers and determine why are they wrong. And students, I would always suggest that you do that. In pretty much all the coursework, just because you may not see multiple choice questions on this year's AP exam doesn't mean that you can still study them. You can still use your books and whatever and study them, but really analyze why multiple choice choices are incorrect. Okay. Next, I want to kind of show you a series of problems that I'd like you to try on your own. I'm not going to read through them, but they will give you a little bit more practice with the idea of arc length. And it's written very special that you can do this without a calculator. So you can take a look at number 2. It's in our documentation. And number 3 is a wonderful problem. I'm going to have you guys probably take a look at this one as well on your own. If there's a single problem outside of the warm-up that we definitely want you to do before the next lesson, I would really strongly urge you, both teachers and students, to take a look at it. It's a wonderfully written problem. Brian put this one together, and it's got a lot of moving parts to it and a lot of really neat nuances and potentially false. But I really love the content here. And then here's probably the granddaddy of them all. If you want this extra challenge, another great problem here. It's a problem that is certainly not lacking in multiple representations, right? You got your table of values, you got your piecewise function, both graphically and sort of analytically. And essentially what you're supposed to do is find the total distance that the particle will travel from this point all the way to this point. And you're going to be sort of interweaving a lot of these multiple representations, and that's another great problem, right? A solution guide, remember, can be found by clicking the link that's in the description below. We don't have them at the time of this actual live session, but they should be up by the end of the day, both for probably yesterday and today, and then we'll try to populate them at least within 24 hours of our sessions. And I want to give a special thanks to Mr. Ted Gott. Ted has been so gracious to kind of do our quality control, and he's providing some tremendous solution keys for us. Ted hails from Galesville, Maryland. So thanks, Ted. So we wrap up for our debrief and summary. Basically, our enduring understandings, the things that we want to make sure that we take away from this is that definite intervals will allow us to solve problems involving the accumulation of change in length over interval. That's the main purpose. That's why we study them. And then the arc length formula for takeaway and speed, the arc length formula is expressed here just as we saw in our development of earlier in our speed formula. So those are things that you're going to use in calculus in general. And our common errors or misconceptions or pitfalls. Well, you got to be careful to compute the derivatives carefully. Think about how many times you saw some very tricky chain rules today. So it's easy to miss those. Often the phrases find the length of the curve, find the perimeter, determine the total distance traveled, all are synonymous with finding the arc length. And the boundaries for the arc length formula are typically going to be parameters like t or theta. So you want to be used to that. All right, the AP exam practice, your true homework here is a wonderful problem. The problem's not very old. This is something Brian and I worked on. Brian, for the most part, put this guy together not too terribly long ago, and it reads really well. It's a very interesting question here. You got two particles P and Q moving in the xy plane at time t equals 0. Particle P is at position 0, 0. Particle Q is at position 3, -2. The position of particles P and Q respectively at time t are given by these expressions. You don't want to be afraid of these expressions. I know they have a lot of letters, but they're there to really define that this is the position of part P. This is the position of part Q. Subscripts are a good thing. For particle P, the graph x prime sub P of t is given above, and we're told that y of P of t is this expression 3t over the derivative of x at t for particle P. Particle Q, he says the graph of yq of t is given, and yq of t is x prime sub P of t. So a lot going on here. And then we have a piecewise definition for our x prime Q of t. Now the two questions that we're going to ask are just simply find the speed of particles. So it's a typical type question. And for B set up, but we're not going to worry about evaluating an expression that involves one or more intervals that would give this total distance traveled. Okay? So two ideas that definitely came from the lesson in 9.3 that are going to carry over nicely. All right. So definitely like you to work through that, and Brian's going to go through that solution first thing in the next lesson. All right. Before we close, we want to make sure that we point out the fact that we know that not all students may have access to the internet or device. Now, if you're obviously watching this, that's probably not the case. But whatever the event is, we're working on solutions. The College Board wants everybody to have access to these. That's always been their main goal is that equity across everybody involved, all the stakeholders. So if you need mobile tools or connectivity, or more importantly, if you know somebody that does, if you can have some way to contact them, they can reach out directly to College Board. You just kind of jot down that little web address, cb.org/tech, and they will certainly work really hard to try to remedy that situation. Right? There's a lot of instances where there's a lot of internet companies that are providing free service during this particular time. All right. Again, it's certainly been unusual. The circumstances that brought us all here together kind of brought us together as a community of both teachers and students. And just please know you have a lot of people that believe in you. Brian believes in you. I believe in you. Your other AP virtual teachers believe in you. I'm sure that your classroom teacher does as well. And we just want you to think about turning the situation into a bright thing. This is a bridged exam. This could be a positive thing. That your focus can be a little bit narrowed, and you can do well in this. We really feel that you can. And we want to make sure that all those years that you've worked hard in mathematics to get to calculus BC pays off. All right. Brian's going to be back with you tomorrow. He's going to be talking about 9.6, solving motion problems involving parametric equations and vector value functions, and it's going to probably tie into a lot more integration. But until next time, I want you all to stay healthy, stay safe, and keep learning.
Well, good morning, everybody, and welcome back to our Friday edition of AP Calculus BC Live. If this is your first time joining us, I want to welcome you and introduce myself. My name is Brian Passwater. I'm an AP Calculus teacher at Speedway High School in Speedway, Indiana. You can see on the screen, on the bottom corner, there's our logo. You might not be able to tell what it is, but it's a spark plug. We are the Speedway spark plugs because we are right next to the Indianapolis Motor Speedway in Indianapolis, Indiana, which is the home of the Indy 500, which is commonly known as the greatest spectacle in racing. I want to give a big shout out to my AP Calculus students who are enjoying the first day of their well-deserved spring break starting today. And I'm sure, like many of you, they've been working incredibly hard these past few weeks as we've been learning together how to navigate and do all this e-learning and distance learning. For my class, I don't know about you, but we've been doing some live Zoom sessions daily, kind of like we're doing here, except for my students are able to more interact with me because we don't have 2,000, 3,000, 4,000 students on at a time. And I don't know if you guys are anything like that at your own school with your own teachers. I know that some schools aren't allowed to have any instruction right now. Some schools are. But it's always interesting to me because for my own students, every day we on Zoom, and the very first thing we ask, right, you were saying about calculus, about the homework. Now, the first thing we ask every single time that they ask me is, what do I have for breakfast? We have morning sessions. They always know what I have for breakfast. And so this morning, in case you're watching, I had a nice little V8 for breakfast this morning, a couple of oranges. So I am geared up and ready to go. So I hope that you too, because we're going to have a really great session today as we wrap up our discussion on parametrics. And so before we get into all of that, I want to show you something. Look at this. This is a screenshot from Wednesday, right? So we started these live sessions on Wednesday of this week. And as we were planning these, as College Board was planning these, this is not something that had been in the works for a year or 2 years. This is something the College Board decided they wanted to do with all the schools being canceled and a lot of the anxiety that was going on around with teachers and students about, I've been working so hard for 7 months. What's going to happen with AP exams? I can't be in school. How am I going to be ready for this test? And the College Board really said, look, we got to do something. So they found some presenters and teachers to say, would you be willing to step in and do some live virtual lessons that we recorded for our students to get them ready, not just to learn the rest of the material during the curriculum, but also to get them ready for the AP exams the month of March and May, or March and April leading up to May. So we kind of just jumped into this. And so I remember on Tuesday, the night before we were getting ready to have our very first session, I was talking to my wife, kind of getting ready in the evening, and she knew that I've been working on these sessions with my co-teacher, Tony Record. Maybe you saw him present yesterday. And she knew that we were working on these things, and she kind of started asking questions about it. And it occurred to me, I didn't do a very good job of explaining to her what was going on because she knew that I've been doing Zoom sessions with my own students, and she knew that this was going to be cast on YouTube Live, but we're using Zoom as sort of an intermediate app to get us there. And my wife thought I was talking to my students today. So I guess you guys are also my honorary students today, whether you're a student or a teacher. But we were talking about it. I couldn't figure out whether we were going to have 10 students doing live, 50 students, no students, 100 students, but never in my wildest dreams did I ever imagine that on Wednesday live at 9 a.m. 6 a.m. on the West Coast, we have up to 4,500 of you joining live for the first Calculus BC session. And on top of that, in the day and a half since we ended that session for our first one, we have over 45,000, 45,500 of you have viewed the video. Maybe just a couple of you disliked it so much you watched it like 100 times in a row. I don't know. But 45,000 of you have watched this. And it's not just AP Calculus. I went on the YouTube channel for College Board today, grabbed a couple of screenshots. These are some of the videos for the other AP classes that have happened. You can see these are brand new, 2 days ago or yesterday. 77,000, 25,000, 18,000, 75,000, 40,000 views. And so it occurred to me that just as I'm proud of my own students for all of the hard work that they've been doing, I'm extremely proud of all of you as well. My students have embraced this challenge and they've committed to not letting the circumstances or the obstacles that have come thrust in front of them this spring semester become a barrier or become an excuse. They're working hard to overcome those things. If you're joining us live or if you're watching the recording, you're doing the same thing. So we're very proud of you and we're excited that you're joining us. And we feel like if you join these each day, that you really are going to get better each day. And when the exam does finally come here, you guys will be ready for it. You're going to be successful. You guys will do a great job. So every day that we're on here, we have some materials that you'll see me writing on them, and you have access to those materials. So if you want to get the materials and print them off before the session, so you can follow along with them, or even after the session, if you want to print them off, you can go on the YouTube channel and underneath the title, you're going to see kind of the bottom there a link, and you kind of go right past the thumbs up, right? So you go down past that little thumbs up. Maybe click on that on your way down if you would like to. Maybe by accident, that's okay. But you're going to see this little live link right there, and it's the same link every single day. And then you're going to be able to click on that, and it will immediately take you to a Dropbox folder. And in that Dropbox folder, you're going to see all of our handouts. So each day we'll keep adding them. And also after we add them after the lesson, we're also going to post probably later that evening or the next day the written, actually typed up solutions for all of those problems. So in these ones, we're not going to be able to do every single problem on the handouts. We're purposely including additional questions that we're not going to be able to get to that way. As a teacher or as a student, you can either assign them to your students, or as a student, you can just do some extra problems to get some more practice. But we'll have the typed up solutions there for you to check along the way. And I didn't even think about this, but Tony, Record, the other teacher, right? We each have our own Dropbox Dropbox that we share, teachers and things like that. But we wanted to make sure that we created a different Dropbox that wasn't linking directly to us for these sessions. And so I was making this Dropbox folder last week, and you had to put a name and all that kind of stuff, email address. And so I just wrote down Isaac Newton for the name, not even thinking it would matter. But if you look, when you get that little link, you're going to see the Dropbox folder that says Isaac Newton shared this with you. So I think that's kind of apropos and serendipitous because Isaac Newton is sharing the calculus with you, but now also he's apparently sharing some nice resources, materials that you could use during the lesson and after lesson as well. So what's going to happen today? What's going to happen next week? And what's going to happen down the road? So today is Friday, March 27th, and we are looking at topic 9.6 in the curriculum. This is our last topic that covers parametric functions and vector value functions. And then next week we're going to kick off our beginning of series and Taylor polynomial. So next week it's March 30th, Monday through Friday. So this week we started on Wednesday, but from here on out we will meet every single day of the week, Monday through Friday, all the way through May 1st. And so next week these are our 5 topics. You might see some little asterisks next to some of the topics, and some of them don't have asterisks. What that means is I'm sure you probably know by now that the College Board has worked with some universities to figure out a way to reduce some of the content of most of their AP exams for this year, and this year only due to the extenuating circumstances. And asterisks are the topics that are still going to be tested on this year's exam. So you might be wondering, so today's lesson does not have an asterisk, and a couple of the lessons next week don't have asterisks. What's the point? Why are we doing these lessons on things that aren't going to be on the exam this year? And so it's a really good question. I'm glad I asked it, but I want to make sure that you hear this clearly because there's a lot of good reasons of why we're still covering things that are not going to be on this year's exam. First and foremost, even though it's not in the exam this year, it is in the curriculum, and universities do expect that students will have seen these things and know how to do them as you move on to future courses. And so we're not just trying to get you ready for the exam that's going to happen here in 6 weeks. We want to make sure that you're successful way beyond the exam, so that when you go to college next year, if you take the next course in math sequence, that you'll be in a good position to be successful beyond what we're doing right now. I think that's probably a little bit more immediately gratifying to you as a student or a teacher. These topics that we're doing that are not tested are still really rich, and so we're not covering every single topic that's not tested. We don't have time for that, but Tony and I work really closely with our friends at the College Board and some other math teachers to make sure that we chose some really purposeful topics. So even though they're not tested, we can do a lot of review and AP exam prep, AP exam practice with strategies with them. And if you joined us on Wednesday or Thursday when Tony presented yesterday, you probably noticed that we're doing a lot of things that are tested. So we're doing it in kind of this new context of parametrics. We're reviewing a lot of the things that you're going to see on the exam this year and a lot of strategies. So we're weaving all those things in there, so that way every one of these sessions will not just help you for down the road when you leave high school, but they're also going to help you in May or June whenever you end up taking the AP exams, whenever those are released. So speaking of that, be on the lookout April 3rd. The College Board is going to release some more information about the exams. I know that we're all anxious and excited to see what they come up with. I know they work really hard to make sure they give us a really good test that's going to be measurable of what you actually learned this year. So you earn those credits even working so hard. So we are going to do a lot of things that are going to be helpful on the exam, even if they're not directly tested. And then you'll notice on April 13th, 4/13, I'm kind of fast forwarding a little bit here. We're going to spend 15 consecutive weekdays, right? So three weeks, just doing nothing but AP exam prep and review. And I'm going to tell you right now, if you come to these sessions for the next 2 weeks, and you come to those 15 sessions of 3 weeks after that for their exam prep, it says on their BC exam prep, but we also know there'll be some AP problems on the BC exam. So we'll be reviewing all of those things, kind of tying AB and BC topics together. You are going to be incredibly prepared. I feel like if you can find a way to watch all these videos or join live for these videos each day, you're going to come into that exam and you're going to feel like you are incredibly well prepared for it. Between the efforts of your own AP teachers that are working with you every single day this year, doing an incredible job, as well as some of the things that Tony and I share with you virtually to prepare for the exam. So put that on your calendars. This is going to be an incredible opportunity. The College Board is allowing us. So we are going to jump into the warm up. Now I'm going to get a drink here. I apologize. We started these sessions on Wednesday, and I forgot to bring a drink with me when I started. My mouth got more and more dry as we went. So every day we do these warm ups, and the warm ups are going to be the follow up from the previous lesson. So at the end of each lesson, we're going to leave with an AP exam practice problem, kind of as homework. We really do encourage you to do that. They should take you about 5 to 10 minutes to do. But these problems are going to be really the heart and soul of how do you get ready for the exam? How do you prepare for the kind of questions that the College Board is going to present you with whenever you sit down for the test? And so the best part about these is that every one of these problems that we do are going to be new and unique. They haven't been on an AP exam before. They haven't been in a textbook. Nobody's been using them yet. They're questions that I'm writing, Tony and I writing, that are different, that are connecting ideas together, and they're things that will get you ready for the conceptual depth of understanding that the exam is going to want to see out of you. So we're not going to have you do this on your own right now because they're in the warm ups. We're going to just kind of walk through them together after hopefully you've tried them. But they're really good opportunities to start preparing for the test. So in this problem, I'm going to walk us through it, and I'll go through the answer with you. There's a lot going on, and if you're at Tony's session, you notice that we have 2 different particles. We have particle P and we have particle Q. So there's 2 different things happening. They're kind of moving through the plane. P and Q both are, and we are given some positions. We know that particle P's position and particle Q's position at time 0, and we also know a little bit about the particles themselves. Like for example, we know that x prime of P is given by the graph, and we also know that the graph is simultaneously y of Q. So the graph is the derivative of x for particle P, and the graph is also the y value for particle Q. And then we're given the y value for particle P separately as this quotient. And then we also know that x prime of Q, x is for particle Q, is given by this piecewise function. So a lot of things are happening here. We have lots of different letters, lots of different directions. We've got a graph, we've got some data, we have an equation, a piecewise function. It can be a little bit overwhelming when we first see these problems. So really show you the importance of being well organized, being careful to pay attention to details, reading questions carefully, and then learning to break down what's really important. Right? I think sometimes what happens is we get overloaded, overwhelmed at the questions. I know for years my Calc students have said as we do AP problems, they'll do one, they'll just be completely stumped. They won't even know where to begin. And as we start going over it, I'll kind of share a couple of things about it. And as soon as I'll kind of rephrase or talk about it once and have a different wording, it will click immediately. And the kids will be like, well, they just asked that, right? And the fact is they did ask that, but they did things sometimes in clever and unique ways to see if you really understand what's happening or whether you just kind of memorize a few formulas. And so if you want to be really successful in AP calculus, we have to really get to the understanding of what's going on more than just trying to memorize some patterns and examples. So let's go through this warm up quickly. I think you're going to see some nice strategies that will help you tackle problems like this. And this is probably the very high end of the complexity that you could possibly see, right? Because there's so many things happening here. But you could definitely see, a problem that might have a graph for part of it, an equation, or 2 different particles going on. But kind of put everything together so you can see all the possibilities that you might be faced with. And so in this case, I'm just going to jump into part A. And notice what I'm going to do is I'm going to look at the question and we're going to underline, analyze, and kind of interpret what it wants. And so I think one of the traps that students fall into AP exams is we get so caught up in the information that we try to use that as we're solving the problems rather than just look at the problem by themselves. If we sort of ignore all of this stuff up here and look just at the question, we're going to have a much clearer path of what to do. So don't try to use the information yet. Let's think about what the question wants and not worry about anything else. And so part A says find the speed of particle P. Well, Tony talked about that yesterday in the lesson, right? That in parametric motion, we know that the speed of particle P at time 4, we have a nice formula for speed. And at time 4, the speed formula is going to be x prime of 4 quantity squared. I'm just using our equation or expression for speed plus y prime of 4 quantity squared. And the entire expression is square rooted, right? So that's our expression for speed. And so now that I've written that down, I've ignored everything else, just written that down. And now I've got sort of a blueprint, right? That's why I use blue pen. That wasn't completely, wasn't in my prompt sheet. But we have this blueprint of how to solve this problem. If I'm going to solve this, I got to figure out what x prime of 4 is, and I've got to figure out what y prime of 4 is. So now I know what to look for. And as a matter of fact, I'm going to add one little piece here because since we have 2 different particles, it's important to realize that both of these values are for specifically particle P. And so now I'm going to go figure out how am I going to figure out what x prime of P is. Well, if I kind of look around here, remember the graph they gave me up there, this is a graph of x prime of P. So if I want to find out x prime of 4 for particle P, I say go on this graph when the time when t is 4, which I can see is right there, and I can see pretty quickly that x prime prime of 4 in this case is 2. I'm going to square that value. And then now I have to go and figure out how I'm going to find y prime for particle p. So I'm going to look around for y prime. And I don't really see a y prime anywhere, but I do see right here at least an equation for y, right? So if I want to figure out y prime for p, then I can differentiate this, right? And so y sub p, so y prime of that, I'm going to take this derivative. And I mentioned earlier that all these problems are going to have some good review of things that are tested. Well, here's an example because we have to differentiate this. And because it's a quotient, we're going to have to do the quotient rule. So we're going to do low d high. So we're going to get x prime for particle p of t times, so that's low, right? And then d high is the top derivative is 3 minus high. So that's going to be 3t times the bottom's derivative. And that's going to turn into x double prime of t all over the bottom squared, right? So we have a nice little example. We can use the quotient rule. So even though we're learning a new idea, there's some really good previous topics that are in there that are going to help us review for the exam. And I want to find this value again at 4, right? So it's going to be y prime of p at 4. So I'm going to plug 4 into all of this. And so we're going to get x prime of 4 and then times 3. And then we're going to have 3 times 4 is going to be 12, right? Then we're going to have x double prime of 4 all over x prime at 4 squared. And this problem's awesome, isn't it? I'm just going to figure out who this is. So x prime of 4, well, we already figured that out, didn't we? That was already something we figured out. So x prime of 4 was 2. So we're going to get 2 times 3. And then we're going to have 12. And now we're going to figure out x double prime. So this is another good connection is that if you're given x prime and you want to know x double prime, this is really just the slope, isn't it? Of x prime. And so we're given a graph of x prime. So at 4, the same location, I want to figure out the slope right there. Well, the slope of this line is just -1. So that means x double prime of 4 is -1 all over x prime of 4, which we said was 2 squared. And that ends up giving us, if we simplify this a little bit, 6. And then we're going to get plus 12 over 4. And that's going to be 9 over 2. There we go. And then finally, if we look at part B here, it says set up but do not evaluate. We see those a lot in the AP exam. And we just want to set problems up to see if you understand them. But we're not going to be as interested always in having you complete all these. So let's figure out an expression that would give the total distance, right? So that's a key word there, total distance traveled by particle q. And Tony also taught this yesterday. This is a really good warm-up kind of review what Tony did. The total distance formula is going to be from the integral from 0 to 5, right? And then we're integrating speed, right? That's our formula for total distance. And so it's going to be the square root. And again, we're doing particle q this time. So it's going to be x prime of t for particle q. A lot of letters going on there. And then plus, and then same idea, we're going to do y prime of t for particle q, quantity squared. And then now we're not going to plug numbers into here because we're integrating this, right? In the previous example, we plugged 4 directly in because speed is a magnitude, right? It's a scalar. So we plug something into it. When we're finding total distance, this is now an expression in terms of t. It should have a dt at the end that's integrated. And what we're going to end up doing is we're going to try to find some expressions that we can plug in. We can't leave it like this for the AP exam because we don't have this in terms of just t like we need to. But we do have an equation for x prime of t, for particle q. X prime of t for particle q is this. And notice we have the piecewise function. The piecewise function is two pieces. The first piece is from 0 to 3. The second piece is from 3 to 5. So what we're going to have to do is we're going to have to write our integral up into 2 separate integrals. Another really good review, something that we would learn in the earlier part of the year during the AP portion. You can integrate something to the piecewise function. We're going to break that into 2 parts. So we're going to integrate this from 0 to 3, and then we're going to add a separate definite integral from 3 to 5. And that'll allow us to use those properties of integrals to add up those 2 finite integrals. So x prime of t or x prime of t for particle q. Notice we see that it's just going to be 2 times t there, right? Quantity squared. Then I have to figure out y prime of t for particle q. So I kind of look up here. I'm trying to find particle q, and notice what we have in the graph here is y sub q, right? So from 0 to 3, we see that y of t is this graph right here. I'm kind of highlighting in blue. I'm going to erase the earlier part that we're looking at. This is y. So from 0 to 3, think about y prime would be, right? Y prime from 0 to 3 is just going to end up being 0, isn't it? Because the slope of that segment is horizontal, so we know it's going to be a slope of 0. So this is going to end up being 0 squared. And now we're going to break it up the other part as well. So now we're going to go from 3 to 5, and we have the same idea. We're going to do x prime squared. So now we're going to have sine of t squared. And then same idea for the y prime. But now from 0 to 3, we have the segment right here. And I should have made that in red probably. So if I make this one in red, this is the second part, right? From 0 to 3. So in that part, y prime for particle q, again, is the slope. But it's still linear, and the slope is constant. The slope is going to be a constant of -1. So I can go back up here and then -1 squared dt. And notice the instruction said set up, which we did, but do not evaluate, meaning don't work it out, don't complete it. So we can leave our answer like this, can't we? We couldn't have left it as it was in the beginning because first of all, we can't compute this without breaking it up. And second of all, we can't have functions in our setup. We have to turn things into expressions with only t in them, not x of t or f of x or something like that. So there's a warm up. It was a pretty hardy problem, I think. A lot of good examples in there to sort of build on what you guys did with Tony yesterday. So let's take a look at what we're going to do here for the next 20 minutes or so together. We're going to be kind of putting all these ideas together, right? So what we're going to do, we're going to talk about finding the position of a particle using parametric functions. If you've done particle motion earlier in the year on a straight line motion on the x-axis or y-axis, same exact idea, but now we're going to extend that to parametrics. So we're also going to be connecting the concepts of motion that we've learned. So we've got a little bit of motion here for unit 4 and unit 8 and unit 9. So we're going to connect all those ideas together, kind of look at this more cohesively. So what should you know to be best prepared for this lesson? Well, hopefully you're comfortable with solving motion problems that are straight line motion. That would be in terms of along the x-axis and along the y-axis. You should be comfortable differentiating parametric equations. We did that on Wednesday during our first session. And then also you're able to connect the concept of position, velocity, and acceleration. We know we can differentiate or integrate to move up or down sort of that ladder. So by the end of this, what will you be able to do? So we're not going to actually solve this problem. And to be honest with you, I'm not even sure how nice it would be to solve this. I wrote this problem knowing it'd be here without actually working it out or thinking we're doing it. So I'm curious to see if anybody tries to solve this problem and see what it ends up being. If it becomes nice or even doable. The kind of questions that we're going to see are going to be particles moving in the xy plane. The position is given by the parametric functions x of t and y of t. We know that x of t, the x position, is sine of t squared. And then we don't know what y of t is, but we do know that dy dt, the derivative of y, is directly proportional to y. By the way, I wrote this wording as sort of like a homage or shout out to our friends that are doing the Calc AV videos, Verge Cornelius and Mark Raleigh. If you've been on their sessions yesterday or even on Wednesday, they were talking about interpreting these differential equations like this. There's been a lot of problems like this. So if you were in their Wednesday session especially, you should be really comfortable writing that. So at time 0, we were given a position, and we want to know what the position would be at time 4. So really the question today, the only new idea that we have to sort of extend our learning with is going to be how could we find the position of a parametric form by extending our understanding of particle motion. I keep saying the word extending because if you've done the particle motion earlier in the year, a particle or bug is moving along the x-axis. This is the motion that we see in a typical Calc AB course. If you've done that motion, then you have all the tools that you need to do parametrics. You're going to do all these problems just by doing these as treating as x and y as 2 kind of separate problems. So you're going to find these problems probably very doable. So let's look at a couple of examples. And before we jump into those, I want to point this out again. This is in the Dropbox link, right? All these materials are in the Dropbox link. But I made a little kind of one sheet or a quick sheet I call for my kids, right? Kind of take all these big ideas. So we might spend in class 2 weeks, right, doing parametrics, all kinds of stuff. And so you have all these different notes and handouts and you have formulas on different ones. But it's really nice at the end of it all to have a nice one page with all those ideas, those big concepts, the formulas together in one place, right? So these are kind of the big ideas that we're talking about position. We're using vectors, right? We talked about the word vector yesterday. Essentially, we're looking at it as an x coordinate and a y coordinate, but each of those is defined by time rather than each other. And so x of t is our x coordinate and y of t is our y coordinate. And then we can find the position. And this is just the x position, right? So if we're trying to find the position of something, we can use our sort of accumulation model. In our accumulation model, we have x of a plus the integral from a to t of x prime of t dt, right? So we have to find any value of any function. It's going to be a starting value plus the integral of the rate of x prime. And we can do the same exact equation with y to figure out the y coordinate. It would just be kind of parallel. that y of t, the y position, is going to be a starting y value plus the integral from a to t of y prime of t dt. So that's what I mean when I say we can extend our understanding, because we've done these kind of problems earlier in the year with Calc AB, and now we can just do them separately to figure out how to do the same exact problem in parametric motion. We know the velocity vector is just going to be the derivative of the velocity in the x direction and the velocity in the y direction. We can write that as y prime and x prime, or we can write it as dx dt and dy dt. You can be ready to see both of those. They're the same ideas. And the acceleration vector, as you might imagine, is just the derivative of that. And so x prime becomes x double prime and y prime becomes y double prime. And as Tony talked about yesterday, we have this idea of speed in parametrics, and speed in parametrics is just the square root of dx dt squared plus dy dt squared, which leads us directly into our total distance traveled, and that's just the integral of speed, which is the integral from a to b of the square root of that speed expression that we found. And then on Monday, or on Wednesday, we keep thinking that we started on Monday this week, but on Wednesday during our first session, kind of led us through the idea of dy dx, which is the slope of the tangent line to occur. And the slope of a tangent line is always dy dx, but if we're given parametrics, we can find that by doing dy over dt divided by dx over dt. And this little last piece here, kind of snuck it in at the bottom, hoping maybe you wouldn't notice. This is how we find the second derivative with respect to x. This was that topic 9.2 that we kind of skipped over because we only had a few days and a few topics that we covered. But Tony and I are going to be making a little supplementary video. They'll put in that same Dropbox link. When you go to that link, you'll see a folder that says supplementary videos. And we're going to end up putting one of those in there, maybe 10, 15 minutes, kind of walking you through this idea and giving you a couple examples for it. That way you'll be, be exposed to them and kind of see how to do them. So with all that information at our fingertips, let's try a few of these practice problems. And again, we're going to incorporate a lot of things that are things that you know from earlier in BC or AB, mixed in with these ideas of parametric equations, as well as combining a lot of the skills and the mathematical practices that the exam is going to test you on. So one of those is going to be seeing things in different forms, whether it's graphical or algebraic, whether it's dx dt or y prime. All these things are going to be things that are going to be helping you prepare for the exam. So our first example we're going to do together is the position of a particle is defined in parametric equations as x of t and y of t. We have our x value and our y value, and dx dt, so that's kind of x prime, right? We talked about another way of saying x prime of t is given by this, and dy dt, y's derivative, is given by the picture. So we don't have an equation for it. We have a nice little graph of it, and that's why it's labeled as y prime up there, right? Because that's the same thing as dy dt. And it consists of a line segment and a semicircle, and we know that at time 3, at t equals 3, the particle is at this position. So that means that x of 3, that's our time, must be 7, and y of 3 is going to be equal to -1. So we're going to find the position at time 0. So if you remember from the previous slide, we talked about how to find the position, right? On the previous slide, we learned that the position of a function is just going to be the initial position, and then adding to that the integral from the starting time to the ending time of the derivative of that function. And luckily for me, my pen decided to freeze up here for a second. So let me see if I can unfreeze myself here. Wonderful. I don't think it wants to unfreeze for me all of a sudden. There we go. Sometimes when you get on these smart notebook files, you do a lot of things at once. It kind of freeze up on you. So there we go. So I want to find the position at time 0. We're going to have, let's find the x value first, right? So I think with parametrics, the big key is realizing we're just going to find the x position and we're going to find the y position separately. Okay, so to find the x position at time 0, we're trying to find x of 0, and x of 0 is going to be the starting position. Well, what do we know? We know that x of 3 is 7, so it's going to be x of 3 is my starting position plus the integral from 3 to 0, my starting position to what I want to know. And I realize those are kind of reversed right now, so we can deal with that here in the next step using some properties of integration of x prime of t dt, right? So to find the value of any function, we have a starting value plus the integral of the derivative or the rate from the starting time to the ending time. And so in this case, I'm going to find a way to integrate this. X of 3, by the way, we know is 7. And I'm going to go ahead and subtract, right? We can flip those limits of integration using our properties of integrals. I want to reverse those so that there's a lower numbers on the bottom. I just make the integral the opposite. And then x prime we're given, and x prime is equal to at e to the 2t power. And now we got to find a way to integrate this. And so if you're a BC student, hopefully you are right now, what do you think we're going to do, right? Take a couple seconds and see if you can recognize what the best strategy is going to be to solving this problem. So I'm going to give you about 15 or 20 seconds to think about this for a few seconds. So whenever I see an integral, my first instinct is thinking u substitution, because that's pretty much the dominant way that we integrate things. But in this case, it's not going to quite work out because of this extra t that we have in the problem. And hopefully you recognize it's kind of like a product, isn't it? And we have a product of two things, so we can't use u substitution. Typically for Calc BC at least, that's going to end up being a integration by parts problem, right? So I'm going to do this tabular method. Hopefully you've seen that a little bit. The tabular method is a nice way for us to kind of organize things and keep things clean, especially when your u is going to be a polynomial, something x or x squared or something. So in this case, I'm going to make the u for integration by parts just be the at, and then I'm going to make the e to the 2t become my v prime. And then the way we use tabular method is whatever you choose for u, just keep differentiating that until we get down to 0. So at becomes just 8, and then 8 becomes 0. And if I'm integrating this, the integral of e to the 2t, we could do some u substitution, but it kind of helps understand the properties of how integration works and how u sub works. U substitution for integration really is just the inverse or the reverse chain rule, isn't it? And so instead of taking the derivative of e to the 2t, we're integrating it. So we know when we integrate this, it's still going to be e to the 2t, but instead of multiplying by 2 like we would if we were differentiating it, since we're integrating it, we're going to divide by 2 or multiply by a half. Then we have to do it again, right? We go all the way down to we kind of have our 0, we match our 0 term here. And so I'm going to integrate this again. Well, the integral of e to the 2t that we just said was e to the 2t times 1/2. We already have a 1/2 there, so now it becomes 1/4. And when we use the tabular method, we use alternating signs, and then we kind of connect these diagonal terms, and the product, the sum of those products are going to end up being the indefinite integral, right? We could have easily done this by using the integration by parts, the formula as well. Sometimes doing things tabular method on problems like these make your life a little bit easier, quicker, although we still do know the formula for problems as well. So in this case, we're going to get, if I integrate this, 8t times 1/2, that's going to give me 4 times t, e to the 2t power, and then minus 8 times 1/4, which is going to be minus 2 e to the 2t power. So this is what we get from this integral here, but we're integrating from 0 to 3, so I really need to put my limits on there. And if I plug in these in, if I plug in 3 first, we're going to get 4 times 3 is 12, e to the 6th power, and then plug in 3 to the second one, we're going to get 2e to the 6th power, and I'm going to subtract. You know, I put an x here, didn't I? You get so easily caught up in writing x all the time, it's easy to slip in there. And then we're going to plug in 0. If I plug in 0 to the first term, well, 4 times 0 is going to be 0, and then minus 2e to the 0 power. Sometimes I have to remind my students that when you plug 0 in, a lot of times it just becomes 0, but not all the time, right? So you can't just automatically assume if you're going to have 0 for one of your limits, the answer is going to be 0. It doesn't always work out that way. So in this case, we have 12e to the 6th minus 12, or 2e to the 6th. That's going to be 10e to the 6th power. And then in the other parenthesis, 0 minus 2e to the 0 power. Well, 0 minus 2e to 0 is just going to be -2 inside of there. And now I'm going to combine these, and we're going to get, kind of move up here this line. And we're not going to forget about this little thing here in front, are we? So in front of this, we have 7 minus quantity. All this work we were doing was just to figure out what this integral was. So I'm going to make sure I put that in brackets. 7 minus 10e to the 6th power plus 2, because I'm going to distribute that negative sign. And then I can distribute the actual subtraction sign, and we're going to get 7 minus 10e to the 6th, and then minus 2. That's going to give me 5 minus 10e to the 6th. All of that was our way of finding what x of 0 was. So that's a lot of work. Hopefully finding y of 0 won't be quite as bad. I'm going to do that in red pen, so that way we can kind of keep these two ideas separated, right? So y of 0 is going to be the same general idea. Y of 0 is going to end up being y of 3, because that's the time that we are told, right? Plus the integral from 3 to 0 of y prime of t dt. And then this time we're actually given a graph of y prime. And so finding the integral from 3 to 0, I'm going to go ahead and again use that same property of limits. It's going to be -1 minus the integral from 0 to 3. And now I got to figure out what that integral is from 0 to 3 of y prime. Well, this is the graph of y prime, and I'm going to do this somewhat quickly, so that way we can kind of jump ahead here in a second. But finding the definite integral is finding the signed area. So this is kind of a weird shape. So how am I going to find out the area? It's finding the area, the signed area between the curve and the x-axis. And so really it's going to be this shape right here, this little triangle. And then whatever this little shape is here, it's like a wedge between the circle. And the same idea here. Well, how are we going to compute that? How do I come up with that? Well, the triangle part is going to be fairly easy because for this part right here, since it's below the x-axis, it's going to be negative. And we're going to have negative 1/2 base times the height. So it's going to be negative 1/2 1 times 2. And then the rest of the stuff is still below the x-axis. So it's going to be minus again. But here's how I'm going to approach this problem. Maybe you do it a little bit differently. If I want to figure out this red part, I'm going to think about this as a big rectangle. And then I'm going to cut out this sort of half circle inside of it. So I'm going to think about this as how do I figure out the area of the red part is going to be the rectangle. The rectangle there is going to be 4 times 2, right? Base times height. And then I want to cut out this half a circle. So I'm going to cut out a 1/2 pi r squared. And r in this case is 2. We can see that pretty easily. And then that entire thing, right? 4 times 2 minus the half a circle. That will give me the red part. But since this was underneath the x-axis, that's why I am subtracting it. And so if I bring back what we had in front, right? We had a negative 1 minus all of that in front. So this is going to be a little bit ugly, I think. And thank goodness on the FRQs on the exam. We don't really have to simplify on the FRQs, but we're going to have negative 1 minus all of this whole thing. Negative 1/2 times 1 times 2 gives me negative 1. And then this is if I distribute this other minus sign here, it's going to end up becoming plus 8 inside of there. And then, sorry, that's still minus 8, isn't it? I'm a little bit ahead of myself. This is a minus 8. But then negative times negative becomes plus. And now we're going to get 1/2 pi times 2 squared. And we can simplify that. I'm going to not simplify it now because of time. But if you look on the answer keys that we have that we'll be posting to that Dropbox file after this, you'll be able to see the simplified answer. And then we can find the answer to the question because we want the position. The position is going to be the coordinate that we found here, right? This is our x of 0 position. And then we can write that as an order pair. We can write that as 5 minus 10e to the 6 is my x coordinate. And then our y coordinate was this expression right here. And because I ran out of time, we'll do that. Please on the AP exam, don't draw an arrow to a blank space. Go ahead and make sure you show all your work. Okay, so I'm going to highlight a couple more problems that you can try on your own. The next example is now we're starting to take things that Tony did that I did on Wednesday. We're blending them together. And so this is a really good table problem. It involves acceleration and it involves velocity when the particle's at rest. So try this problem out. The algebra is pretty straightforward on this one. It's not a really heavy algebra problem like the last one was, but it really makes you, connect some ideas together. So that's a really good problem to try. We also have a problem involving speed, but instead of giving you time and you find the speed, we're going to make you do this in reverse. We're going to tell you the speed, and you're going to go backwards using that same speed formula to see if you can figure out what the time was. Another really good problem that doesn't require heavy algebra, but there are some really neat connections in there. And then in the file, if you have printed it off, you see it. It's got a card sort there. And what you're going to see is this is one example where I'll give you 5 Roman numerals, right? So we have this practice stem here. So any given time, particles moving along a curve with that position, and we're given some information about x prime and y prime. So we're given both of those derivatives, and we're also told where the particles at time 2. And so we're not even solving these problems, we're just getting the setup, right? So the most important part of any AP problem is just understanding what it's asking and what approach you should take. And once you can do that part, then all of that skill, all that practice you've been doing all year is going to kick in. You can start doing the derivatives and integrals, things like that. But this is, which one of these would tell us the total distance traveled. So there's a lot of small mistakes. So there's a lot of answers here that are close, but not quite right. Tony did a similar example in yesterday's notes for that as well. And then on the next slide, this is the rest of this card source. So there's actually 5 Roman numerals. They're asking you to find 5 kind of similar ideas. This is kind of encapsulating all the things that we've done. And there's several different choices here, A through, I think it's A through Q or something like that. And so you're going to look for these choices and figure out which one matches up with each one of those choices. And so you'll be able to hopefully kind of drag them over. So x of 5, we kind of mentioned a minute ago, how would we compute something like that? Well, we would take a starting value, which is going to end up being x of 2, which is 1, and then we're going to add the integral to that of x prime. So a problem like this would go together. But a common mistake that students make is something like this choice D, because they mix up the 1 here, the x value, with the time value here. So it's kind of a nice little card sort. It doesn't require you to solve things out. So make sure you kind of make those connections so you can really get a lot of good practice by trying to figure out which ones go with what. And then I have to give a quick little shout out to this little field goal problem. Jenny and Ben are practicing field goals, and you're going to figure out based on the information whether he's going to clear the uprights or not. One little thing I'll point out to you to be careful for is the equations are in yards, but the uprights are 10 feet above ground. So whatever answer you get, you have to be careful to make sure that you're not answering yes or no without thinking about if you're in the same units or not. And those problems again are going to be worked out in the solutions for you as well. So a couple more nice little practice problems that you'll be able to do. And I think you'll end up seeing a lot of good examples that you haven't seen before. There are some things that are similar if you've done some AP problems or book problems, but I always try to throw in twists you haven't seen or see things in new ways because the AP exams are going to do that, right? We know the exams are going to show you things in ways that you haven't seen before. So you don't want to get ready for that. How do you get ready for something you haven't seen before? Well, it's to practice things you haven't seen before. The more you practice and adapt and understand and make those connections, the better you are to be able to do that on the actual exam. So today, what we ended up doing was we made a lot of these, hopefully some connections, wrapping some things together. We looked at finding the position of a particle. A couple of things to pay really close attention to, not just with parametric motion, but really on the whole AP exam is pay really close attention to what function is given. Go look at a bunch of AP problems. Go look on AP Central at FRQs. And here's what you're going to notice. Almost every single problem, they give you something, right? A graph, a table, or an equation, right? A graph of F or a table of F or an equation for F. And you look at the questions, they never seem to ask you about F. They never ask you about what you've been given. They ask you about something else. Here's a graph of F prime. Tell me about F. Or here's a graph of F. Tell me about G, right? They're always going to see if you can make those connections between things. So pay really close attention to what function you're given and what you're being asked for so you don't fall into those easy traps. Be careful about finding position, which we did today, versus finding the distance traveled. Those are very different ideas. Think about the difference between speed and parametrics. That was just a number, right? Speed is a scalar. It's like it's a number. But velocity is a vector, so it's going to be an equation. Typically in parametrics, it's going to be a different equation for x and for y. And then the slope of a tangent line, even though we're in parametrics, doesn't change the meaning of a tangent line. When we talk about tangent lines to a curve, even if it's parametric, the slope of a tangent line is always going to be dy dx, and we talk about how to find that. So this is going to be your AP exam practice problem. And if you're still on, I want you to hang on a second. I'm going to show you something at the end of this slide that's going to be really important. I hope that you stick around for one more minute to check here before we jump onto your other AP sessions. But I wrote this problem late last night. I was inspired because there was a bug crawling across my actual computer screen, and I ended up disposing of it, and it left a mark on my screen. I was like, I should pay tribute to this bug for giving its life for you. So in tribute to the bug, I say bug, we're talking about like a, I thought it was an ant at first, it was very tiny. And so a bug is walking along the door, and I kind of drew this graph of this bug walking, and it ends up being knocked off of the wall eventually. So we got some nice little questions to wrap up. We talked about yesterday and Wednesday. This question is going to be really key because on Monday we start with series and convergence and all that beautiful concepts that come with them. This is going to be a really good lead-in for that. It's going to get us jump started to that. So take a second and try this problem sometime before Monday. So what I want to share with you, I hope you stay on for this, is I want you to tweet out. Okay, I was probably supposed to get more permission. I'm not going to go for this. If you don't see me for the rest of these several weeks, then you're going to know that this is probably a no-no. But I think we're okay. This is my Twitter handle, passwaterb, and then as well as my friend Tony's Twitter handle, it's AP Calc Teacher abbreviated. We're going to tweet out and go ahead and tag us if you don't mind. But use that hashtag. If you're a student, hashtag AP Teachers Rock and teachers, hashtag AP Students Rock. And what I want you to do hopefully is everybody right now is we're a little bit stressed, we're trying to figure all this stuff out, and everybody's working super hard. I know that you guys as students are working really hard right now. Teachers are working so hard trying to make this work for everybody. So tweet out what you appreciate and love about your AP Calculus teacher or students. So if you're a student, tweet out what you love about your AP Calculus teacher or any AP teacher really. And kind of tweet out, tag me and tag them. Each day, we're going to start out these sessions by reading some of those off, and we'll probably end up not identifying names in schools, different types of privacy and things like that. But we want to read off the things that you're saying. We want to read off what is good news right now, what's positive, and what should be highlighted instead of all the unknown and kind of the uncertainty. So tweet us out. We want to see what you have to say. say, tag me, tag Tony, take a photo of this if you want to. That you can get it. But we want to make sure that we share this. We'll keep doing this all the way until May 1st. And I hope that we can start a trend of people sharing all the great things that are happening with you guys and your teachers. That way we can share them out. A very important announcement from the College Board that Tony shared yesterday, but we continue to share. Look, we realize that not everybody has access to the internet, and this exam is going to end up being online, like we know. And so if you know any students or you are a student, please get this information to them. It's a simple website there at the bottom, cb.org/tech, and they're going to find ways to make sure that you have what you need to take the AP exam. So that's going to be highly important. And then finally, thank you for watching. Tony said it best yesterday. We are incredibly amazed at the response of people that have been watching these videos. Look, Tony and I are just classroom teachers or regular guys, but we're so impressed with how many of you are doing so much there. So every day for AP Calculus BC and all your other AP courses, find a way to get a little bit better. Right? I always tell my students, 1 point better today. If you get 1 point better every day, every session that Tony and I give, if you get 1 point better, that's 28 extra points. If you do that, you are going to be extremely successful on the exam. So thank you so much for watching. Don't forget to tweet out. I know already that there was a mistake in that warm-up on part A. I forgot to finish it. And I will make sure that the key has the completed solutions for you. That way, if you did finish it and you caught the mistake, you compare your answer to that. So don't forget, Tony will be here Monday next week at 9 a.m. And Tony will be giving a great lesson to introduce us to series, and we'll see you then. Have a great day.
Once again, hello everyone, and welcome to AP Calculus BC Live. As you can tell, that the chimes indicate that it is 9 a.m. this morning, and it's a pleasure to be here with you once again, whether you're watching live or on demand. We certainly hope that you had a great weekend and that you and your families are safe and healthy, and that you're ready for another week of some great AP Calculus BC content with Brian after the week. So, as you can see, the topic for the session this morning is defining Convergent and Divergent series, which really serves as the introductory concept to this final unit in the College Board Curriculum Guide, Unit 10. And it's quite possible that some of you may have been exposed to this idea prior to your school's closing, but it's also very likely that this is something that could be completely new to you. So, for that reason, we're going to kind of slow this down a little bit. We're going to break it apart, and my goal today is to kind of demonstrate practical usage for the infinite series and then sort of kind of develop that into a more conceptual understanding. Although this particular topic specifically isn't going to be tested on this year's advanced placement exam, you will find out that it does lay the foundation for 5 other topics from Unit 10 that will be tested, and we will certainly be taking a very close look at those over the next couple of weeks. Once again, if you want access to the materials that accompany any of our videos, it's still not too late if you want to try to print this out really quickly, because I've got a few other housekeeping things to address. But if you just simply go to the description in any one of our videos, you can see that from this video, this screenshot is from Friday, but every single one of the videos has the helpful URL link there at the bottom, and you can just click that. Isaac Newton will share a folder with you, and in that folder you can see a list of all the different dates and topics you can download the PDF. Once again, my name is Tony Record. I'm the calculus teacher, or one of the calculus teachers, I should say, at Avon High School in Avon, Indiana. And the students at my school are on spring break. In fact, we have a 2-week spring break, so they're right at the halfway point of that. We were doing e-learning for a long time. I think we were the first school in the state of Indiana to begin our e-learning instruction, and I was kind of missing my students, so I reached out to them over the weekend just to kind of check on, make sure that they were doing okay. Many of them have been watching, some of them are watching now. Thanks guys, it's great to have your support. And we got on the subject of this whole idea of YouTube Live and what this experience is like, and the idea that you as students, and in some cases as teachers, really don't know Brian and I very well. You've seen us through a couple of sessions. Hopefully you'll get to know us more and more as we move through these 28 lessons. But they said, they probably ought to know some things about you. And I thought, well, why is that important? So I did ask, I did ask, well, if you were going to share something about me, what is it that you would share? And one of them wanted to make sure that I conveyed to you, and I'm going to read this. We sincerely apologize to everyone watching about Mr. Record's lame jokes, but after a while you tend to get used to them, or you just find a way to block them out altogether. Regardless, we still love him nonetheless. Okay, thanks guys. And then the second and final one here is kind of a funny one. It says, while we are all social distancing, I love seeing students that I consider my peers from far and wide working hard on Calculus BC instead of letting the situation get in our way. I want to wish everyone out there the best of luck in preparation for your AP. So that's kind of nice sentiments from my students. So if we look at some of our upcoming lessons, you've got the week planned out ahead of you. And as I said today, we're going to define Convergent and Divergent infinite series. Tomorrow, Brian's going to come on and talk about the alternating series test and getting into all the nuances that are associated with series that do have alternating signs. And then throughout the rest of the week, we'll follow up with Harmonic Series, P series, comparison tests, and working with geometric series to end the week on Friday. And then jumping ahead to the week after, you can see that we're going to focus a little bit on Convergence of power series and really all things Taylor polynomials, Taylor polynomial approximations that play a critical role in Calculus BC. And then we'll end with the alternating series bound next Friday, and then that will take us right into our 3 weeks of solid AP Calculus BC exam, right, particularly geared towards this particular year's exam and its nuances. Once again, anything that's marked with an asterisk means that it is going to be tested on the 2020 AP exam. All right, so with that, let's go ahead and take a look at this wonderful warm-up that Brian presented to you guys on Friday. I believe it was about an unfortunate little bug that was walking around on a glass window. So it says for a time between 0 and 8, the bug is walking against glass doors, following the path sketched in this case to the right. The position of the bug at time t is modeled by x of t, y of t, where y of t is t squared over 10 plus 1, and dx over dt is -5 sine of t. At time t equals 0, the bug is at position 11, 1. And you're asked to find 3 different things. The first thing is the horizontal movement of the bug to the left or the right at time 5, pi over 6, and explain your answer. And in part B, find the position of the bug at time t equal pi. And then finally at time t equal 8, the bug gets knocked off the glass and falls into the grooves into the door track on the ground. The bug continues to walk along the ground while stuck in the door track. For time greater than 8, x prime of t, y prime of t is the position 40 over t squared, comma 0, or I should say is the velocity vector 40 over t squared, comma 0. Right, but do not solve the equation involving an integral expression that gives the time c when the total distance the bug walks after falling to the ground is 5. So perhaps you had a chance to take a look at this over the weekend. We're going to go ahead and break it down and solve it for you. So first of all, for part A, is the horizontal movement of the bug to the left or the right at time 5, pi over 6? Explain. Well, because we're talking about this idea of horizontal movement and the idea of left and right, we have to tie this to that velocity of the x position. We're looking at the derivative of x to determine left movement or right. So fortunately for us, we have the derivative of x already provided in the stem of the problem. That is our dx dt. And all that we have to do is figure out exactly what sign we've got here at the time 5 pi over 6. Now there's a lot of different ways that you can use to denote that. This just being one of them. So if I go into this dx dt and if I replace the t with 5 pi over 6, I would have something that looks like this. And then we just have to have a pretty good understanding about what this sign is. Now I'm going to probably take this a little further. I'd like to find out exactly what this value is. It would be good practice for us. Sine of 5 pi over 6, we think about that a little bit. And there's so many different ways that you can pull off this trigonometry. One way you can think of 5 pi over 6 is in the which quadrant here as you go around? Well, it is in the second quadrant, right? Which pretty much tells you that it's going to be a positive value, right? But if you want to get that exact value, you could extend this a little bit and say, okay, well, really what I got right here is an angle, a reference angle that's pi over 6 degrees, 30 degrees, or pi over 6 radians rather, 30 degrees. And then that relates to the fact that the opposite side could be 1, the hypotenuse would be 2. I'm not using a unit circle here, obviously, but we can see that that's going to be positive half. Sometimes it's nice to have that little trig, refresher course every now and then, even in BC calculus. So we end up with -5 halves. But again, what we're a little bit more concerned with here is the fact that we have a negative value. And when we have a negative value, we know that our motion is going to go be going in the left direction. So it does want us to explain that a little bit. So we'll just simply say this bug is moving left at time equal 5 pi over 6. And the reason can certainly use abbreviations like that on the AP exam because, and I'll just reiterate the fact that dx dt, what we just found here, was a negative value at t equal 5 pi over 6. All right. So if we move on to part B, then we're asked to investigate the position of the bug at time t equal pi. Now, because we're dealing with position position that involves two fronts here. We need both a horizontal and a vertical component, right? We're dealing with vectors here. We have two things that we have to find. We have to find a y value at time pi, and we have to find an x value at time pi. Well, fortunately, the y value at time pi, which I'm going to actually find first, is going to be a little easier here because we can see that we got this y equation already presented to us in the stem. So all that we need to do is replace the t with pi. We would have pi squared over 10 plus 1, and really that's about all that we can do with that without the use of a calculator. We'll find out here in just a moment that pi squared over 10 is very close to 1. Pi squared, 3.14159 squared, is very, very close to 10. And so this is probably a value that's somewhat in the neighborhood of 2 when all is said and done. But for the x component, because we are given a derivative of x, we're going to have to essentially undo that derivative. We're going to have to integrate, take the integral of that -5 sine of t, and we will do so with respect to t. And because one of our times, or the time that we're trying to find, is pi, and the fact that we were given an initial position at time 0, it seems very, very logical that 0 and pi should be our boundaries of integration, right? At one of the boundaries, we have information. At the other boundary, we're looking for an answer. So once we have this set up, we know that we can come up with our result, and that would be, well, we're integrating essentially a dx dt. Maybe I should kind of emphasize that that's what that expression really is right there. And that's going to give us an x of pi minus x of 0. Now, this isn't necessarily the way that I show this to my students. I like to illustrate the fact that when we talk about accumulation, this is a situation where we can say that we're really starting with some kind of an initial amount at x of 0, right? So if I were to add that over to the other side, and then I could add this integration, once again, -5 sine of t dt, that is going to equal our x of pi that we're trying to find. It doesn't really matter really how you're going to set it up. You're going to get the same answer for x of pi either way. So if I take the antiderivative of -5 sine of t, what that gives me is positive 5 cosine of t. We have to think there for a moment that the antiderivative of sine is negative cosine, and it's going to wipe out that negative that was at the beginning. And we are going to evaluate this upper boundary of pi, lower boundary of 0, and again, that's going to equal x of pi. And I tell you what, let's go ahead and do what I did down here below. Let's put that x of 0 in front here. All right. So the x of 0 we know was 11, right? That was in the stem of the problem, the initial position 11. And if we evaluate what we got here, 5 cosine of pi, well, 5 cosine of pi is -1, and then we subtract, and then we have 5 cosine of 0. Well, the cosine of 0 is positive 1. We have something along those lines. And by the time we do a little simplifying with this, 11 minus 10 is 1, and that is our value for x of pi. Okay. Now we certainly have the two components of the position on our page, but it would be nice if we could sort of tie those together a little bit and put them in this nice order here. So our final answer would be order pair 1 comma pi squared over 10 plus 1. Now before I move on to part C, I'd like to just really quickly do something kind of similar that I did on Thursday and just give you some visual representation of what's going on with this particular problem. So if we take a look one more time at the graph that I'm going to make here, and this is going to look a little bit like the graph that you saw on the window, a little bit more dynamic, but I'm going to go ahead and put this in motion. But I want to kind of set this up for part A at 5 pi over 6. I want to try to stop this motion and see what's happening. And I went ahead and worked 5 pi over 6 out before the video. I got about 2.6 as a decimal approximation. So if I can set this in motion, I'm going to try to stop this when the time right here is 2.6. Let's see if I can do that. This is pressure. Hey, I got it. All right. So that's what our particle, that's what our bug is doing right there at that time, 5 pi over 6. And we can see he's been moving to the left this whole instance, which reassures what result that we got. Now in part B, we were finding the position of the bug, right, at time t equal pi. So I'm going to set this in motion just a little bit longer. Now I don't want to go too far with it because I'm pretty close to time being pi right now. Now because my increments are set in tenths, I didn't want to keep you guys here all morning watching this bug moving along this graph. Because this is incremented in tenths, I'm going to probably have to stop this at 3.1 and call that close enough. So let's see if we can start it again and stop it at 3.1. Well, okay, that was a fail. But you know what? 3.2 is pretty close, right? It's in that ballpark. But as you can see, that position of that bug is indeed going to have an x value. It looks like it's 1, and that y value, remember, is going to be something pretty close to 2. That's that pi squared over 10 plus 1. And if we kept moving this along, this thing is going to look exactly like the graph that Brian presented to you on Friday outside that window. All right. Okay, hate to spoil the end of the movie, but let's go on to the next problem here. So for part C, at time t equal 8, this poor bug having a bad day. He gets knocked off the glass and he falls into the grooves in the door trap on the ground. And then he continues to walk along the ground while he's stuck in that door trap. For time t greater than 8, x prime of t, y prime of t is 40 over t squared comma 0. We're going to write but do not solve an integral, an equation involving an integral that gives the time c when the total distance of the bug that he walks after falling is going to be 5. So let's see if I can create a little bit more space here, and we'll think about this here. So this goes right hand in hand with one of our lessons yesterday. It's really the length of a curve in parametric. When you're talking about the total distance that we're traveling in parametric, we can use that particular equation. Now that equation is something that won't be tested on this year's exam. It's good calculus nonetheless. But if you recall, it's that equation that says that your distance or your arc length is simply the integration with some boundaries of the square root of your x prime squared plus your y prime squared. And again, that was something that was discussed last week and actually showed up both in video number 2 from section or topic 9.3, and then Brian elaborated on it even more on Friday's video in topic 9.6. So our x prime of t, you can see, has already been taken for us. So we don't have to work very hard to find that. That's 40 over t squared. But remember that we must square that, and then we'll add to that, and the y prime of t 0, and we will square him, and we will extend our square root. We're going to integrate with respect to t, and then we got to throw our boundaries in here. You got to think a little bit about this. It would be very easy just to want to start our integration at the boundary of 0, but we have to remember we're not focusing on distance traveled when the bug was on the glass, but when the bug had fallen into the door trap. So that doesn't happen until time 8, right? The bug fell, he's kind of composing himself, however bugs would compose themselves, and he's going to decide to kind of continue to walk. And we don't know at what time he's going to stop walking, so we call that c, but we know that this is all going to have to equal 5, right? And for all intents and purposes, that takes care of the directive of the problem. I'm going to go ahead and simplify this just a little bit. But it does say that we do not have to solve this yet. We're going to take another look at this here in a moment. But if we just clean this up just a wee bit, we find out that the square root and the square attached to this 40 over t just cancel each other out essentially, and you're left with this. And I'll tell you what, I'll just put the 5 over here for the distance, and that would be an integral that potentially could be solved, and we can find this value of c. All right. So if we look on forward to our lesson overview, what we actually want to do today is I'm going to introduce this concept of infinite series to you, and in conjunction with that, we're going to determine whether these series will converge or diverge. We're just going to start to lay the groundwork for that. There's a plethora of tests that some of you may have already learned. Some of you are about to see them over the next few days. Maybe some of you are working with them now with your teachers in e-learning that are associated with being able to determine whether series converge or diverge. And then we'll talk later on, well, why is it even important to discuss whether these series converge or diverge. As far as some of the things that you should already know, you're going to be exposed to some summation notation a little bit today, so we're going to be dealing with that quite a bit. And of course, the techniques for evaluating limits are going to be very important, especially using L'Hopital's rule from time to time. An example of what you might be able to do after today or the next maybe video or two is answer some practical questions like this. Say if you have a ball that's dropped from a height of 12 meters, each time it strikes the ground, it bounces back to a height of 3/4 the distance from which it fell. The question could be, what is the total distance that the ball travels? And I know that sometimes these what we'll be able to do questions we feature here, we don't really end up solving, but I know that a lot of you from some of the feedback that we've been getting are solving it anyway. That's absolutely fantastic. That's a great problem if you want to take a look at it. All right, now you'll notice at the very outset of the guided practice, we're going to revisit the answer from today's warm-up. That equation that involves the integral expression that gives the time t when the total distance the bug walks after falling to the ground is 5. Let's go ahead and solve this for C, and maybe talk about how this connects to some of the other ideas. So if we were going to go ahead and solve this, and it doesn't look like it's too terribly difficult of an integration problem to take care of, what you want to be careful of though is you don't want to assume that this is a natural log form. Hey, just because we have this variable in the denominator, right? Doesn't matter what power it's raised to, we always use the natural log. If you're a teacher watching this, you know what we're talking about. We've seen students do that from time to time. But let's make sure we understand that that is a t squared. So if this was having a dream, right? If we were dreaming here, this 4 over t squared is really 4t to the -2. So now if we integrate that, we would end up with 40t to the -2. So we have 40t to the -1 power over -1, let's say, right? And then our boundaries of integration are still going to be upper boundary of c, lower boundary of 8. And we know that this is going to be equivalent to 5. Okay, well, the problem says solve for c, so we'll go ahead and do that. And we end up with -40 over t from c to 8. And we plug in our c for the value t, subtract. We do the same thing and plug in our 8 for t. All right, and then I'm going to kind of work up here in this next column so I don't have to scroll down. And we have -40 over c. Let's see, this is a +5 equal 5. Okay, so it looks like those 5s are going to go away. So -40 over c is equal to 0. And then we start scratching our head and thinking, okay, well, what's the value of c here? We can't cross multiply, right? It's very easy to think that this problem has no solution, maybe outside of a calculus course, that's what we would say. But there are a lot of other ways that we can think about it now that we have this power of calculus, the power of the limit, the power of the infinitesimal, the power of infinity. So we can look at this and think, okay, well, wait a minute. If you have a fraction that's going to have a value of 0 when the numerator certainly can't be 0, the only way that that can even happen is if the c value was getting awfully close to a very, very large number like infinity. And now maybe that starts to make a little sense. Oh yeah, -40 over infinity would approach 0. But we have to think about what this is really saying here. We're saying that the time that this bug would have to walk along that door track to achieve a total distance traveled of 5 would have to be infinity. Poor bug. He's going to have to walk the rest of his life. And then we have to address the question, does he really ever reach that total distance traveled of 5? Or does he just approach to it? Or maybe does he converge to that total distance traveled of 5? So it's probably acceptable in this particular situation to say that the limit as c approaches infinity of this quantity is indeed 5. And there's a tie-in that this problem has to some of the things that we're going to talk about. And I think this speaks highly to the fact that my partner, Brian Passwater, is probably the greatest problem writer I've ever met in my entire life. This is a completely original problem that he put together just a few days ago that ties some of the ideas from what we were doing in Unit 9 here as a great introduction to what we're going to get to in Unit 10. So we definitely thank Brian for being able to do those wonderful things. Thanks, I got a little carried away here. As c approaches infinity, I'm sorry, that limit is going to be 0. I got confused. The 5 is the distance that we were traveling, but this actual limit is going to be 0, right? Just kind of getting back to this equation that we have there. So apologize for that. All right, let's move on to our practical use for this. And I tell you, this is going to be kind of interesting here. I wanted to develop a way to really give you an idea about what is the practical application of an infinite series. And I thought about in front of you today actually taking a piece of food, a donut, a pizza, or whatever, and cutting it in front of you and showing you how that can all relate. But for one thing, that would take an incredibly long period of time. And I'm not real keen about using a knife on YouTube Live because accidents happen. This could end up being a very short video because of that. So what I did is I kind of filmed what that particular demonstration would look like. And I'm going to go ahead and show this to you right now. It's going to go kind of fast because I have it in time-lapse mode, but we'll talk about it here just a little bit. But this should set up what we're going to be doing the rest of the time.
Hi everyone, Mr. Record here, a math teacher from Avon High School in Avon, Indiana. And I just got this thinking about something on this Saturday afternoon. I got to thinking about infinite series and the fact that we can add a seemingly infinite number of terms and reach a finite result. So I got to thinking more and I thought, well, what better place to illustrate this crazy math phenomenon than right here in my own kitchen. So let's check it out.
Now, as you can see here, we're going to be dividing a pizza among 4 or 3 students, Alicia, Ben, and Carlos. And there's always going to be a piece that's left over. And we're going to kind of break this down a little bit. But yeah, you can see that trying to divide those leftover pieces into fourths over and over again, it was kind of challenging, but it was leaving very little pizza left behind. So as I said before, we're going to kind of break this down a little bit because I know that video went pretty quickly. And this is outlined also in the handout, if you haven't had a chance to download it yet. But basically, our situation here in example 2 is that we have 3 AP Calculus students, Alicia, Ben, and Carlos, and they're going to take a much needed break from studying for their AP exam. They're going to split a pizza. However, they approach the division of their pizza in a very interesting way. So we initially start by dividing it into fourths, right? We want everybody to have a very fair slice of pizza, but yeah, we only have 3 students. So we have this leftover slice right here, right? That's kind of illustrated there in the picture. And the question in our first recap is, well, how much of the pizza would each student have on their plate after the first cut is made? Well, it's pretty clear that each student would have a fourth, right? And then this leftover slice would be a fourth of the pizza. Well, if I move on to the next cut, I took that fourth, and as you can see up here in this picture that I'm outlining, I cut that fourth into additional fourths, and I'm going to redistribute those. And what happens is I put one of these extra sections on everybody's plate, which leaves this extra leftover piece here. Well, we have to kind of consider, well, how much of the pizza is each of these new fourths? And the answer to that would be a 16th. So if we recap and ask, well, how much of the pizza does each student have on their plate now? We would see that Alicia has, well, originally she had the 1/4, of course, and to that we're going to add a 1/16th, right? And if we want to go ahead and simplify that, I think we probably should. It's going to make things a little bit easier for us to discuss later. We're going to get 4/16 and 1/16, which is 5/16. And I really don't see any need to rewrite that same expression for Ben and Carlos. It's going to be the same amount. Each of those 2 students have 5/16, and then our leftover is still going to be the 1/16. Well, we just keep it going. We're going to take this 16th, and now I'm going to divide this into 4 other equal portions. And if I put each of these on somebody's plate, let's see if I can use a color that shows up a little bit. Put each of these on somebody's plate, and then I have another leftover piece that hopefully we can all understand is, if you have a moment here to think about it, would be how much of the original pizza, and the answer is 1/64. So at this point, how much of the pizza does each student have on their plate after the third cut is made? Well, remember, Alicia and her friends at the very outset of the cut 1 had 5/16, right? That was the 2 original pieces, and then we're now going to add a 1/64th of the pizza. And if we do our common denominator where 5/16 is 20/64, we end up with 21/64ths for each of the 3 students, and that leftover piece is going to be a 1/64th. It's getting smaller and smaller. It's also getting harder to cut, trust me. So if we move on to the next and final cut, that 64th somehow got cut into 4 very, very, very small pieces of pizza, and they were distributed among the 3 students again, just kind of stacking them with the other slices that they had. And that leaves us with this teeny morsel of a slice of pizza left. That would account for how much? Well, 1/4 of a 64th would be 1/256. So basically, if you could eat 256 slices of pizza that big, you would have eaten the entire pizza, I suppose. So we look at how much of the pizza does each student have now. Well, remember, Alicia, Ben, and Carlos from the previous cut had 21/64ths, I believe. And if we add 1/256, and if again you get the common denominator multiplying by 4, 21 times 4 is 84, and then if you add 1, you're going to get 85/256. And I think we're all glad that we're not going to slice this pizza anymore. Trust me, my fingers were glad as well. So we know that each of the 3 students are going to walk away with this much. Now we still have this leftover slice of 1/256. Now, if you think about continuing to cut this little guy, after a while, it's probably going to be very hard to see that there's any pizza left. But there would be these very small, infinitesimally small slices going to each of the 3 students. Well, that kind of brings up the ultimate question here. How much of the pizza will each student actually receive? Well, it seems like they've all 3 have acquired the combined total pizza among them, and they've done so evenly. It only stands to reason that each student would have received a third of the pizza. But the interesting idea is that we were only dividing it in fourths the whole time. And kind of to move from the practical to the conceptual here, those fractional slices of pizza that we talked about, that would be the 1/4, the 1/16, the 1/64. They're called the terms of the series. And then each student's fractional amount of pizza after after each cut. That would be that combined accumulation, that 1/4, and then that 5/16, and then that 21/64, and I think 85 over 256. Those are going to be referred to as what our partial sums are. And because the total fractional amount of pizza each student is receiving is approaching 1/3, we can say that the limit of the partial sums, or the limit of the series, is 1/3. Okay? Now we could do something very similar with another type of food item, and I experimented with this as well. So this time I've got a chocolate cake that I bought, baked, to be evenly divided among 4 students: Alvin, Bianca, Celeste, and DeAndre, by continually dividing it into 5 equal pieces. All right, now I'm not going to walk through the whole process here because I think you kind of understand what's happening. But you can see from the picture I have 4 equal slices for those 4 students, and then on the right is the leftover. And I could ask, well, what would be, they say, the first 4 terms in a general term of a series that would model the amount of the cake that each student would receive after each cut? Well, from the very outset, we can see that each student would have received 1/5 of the cake from the beginning. And then from the picture down below, you can start seeing me stacking other slices of cake, other terms in the sequence. And I think that the one that I circled there blue is actually going to be the next slice, which would be 1/5 of the 5th, which in this case is 1/25. And then I'm going to move to a red pen, and that's up here. You can see that I had the additional 1/5 of the 1/25th slice that I added to each student. And then if I move down here to the bottom, I think that's the next slice when I took that 1/25th and divided that into fifths, which in this case is 1/625. And because the numbers are starting to get pretty rough, I'm not going to go up to the guy, that little teeny tiny piece at the top. But I'm going to say, well, we could go ahead and just add this infinitely until we get to some general term. And that general term, you can see, is just simply a fraction, right? Where the denominator is changing, but the numerator is, of course, 1. And that denominator is changing in such a way that we have a base of 5 because we're dividing it into 5 pieces, but we're just going to use an exponent to indicate the sort of the sequencing of how we are dividing this particular slice of cake. And we could actually find the sum by using some techniques that Brian and I are going to talk about later in the week. But for right now, we can think about this very logically, very practical. There were 4 students that were dividing this cake, and they all got an equal portion. So how much of the total cake will they receive? Well, we hope it's 1/4, right? Because I'd be pretty mad if I didn't get an equal portion of the cake, right, my friends? Now, the actual definition of convergence divergence is outlined in this box, and we can talk about it as kind of relating to the sequence of partial sums, which I'll call S of n. And the summation A sub n would have a limit s. If it has a limit of s, then that series is known to converge, and it's said to have the sum s. So to put it kind of simply, if the limit of partial sums as n approaches infinity is equal to some finite value s, then it turns out that that s is the sum of our infinite series. Now, a few things that you have to be very careful of. Let's say that the limit of those partial sums approaches infinity or negative infinity. Then we know that that particular series is going to diverge. Or maybe it's likely that that limit of those partial sums doesn't exist for some other reason. Then we're going to also diverge as well. So this idea of divergence is going to come to fruition in a lot of our lessons this week. And I wanted to kind of throw in this idea because we don't have a specific lesson devoted to this, the nth term test for divergence. It's probably one of the easier tests to apply. It's one of the earlier tests that you might want to think about using. And it just simply says this, that if you have an infinite series, summation A sub n as n goes from 1 to infinity, we know that that's going to diverge if the limit of the nth term expression as n approaches infinity is not equal to 0. Now, there's a caveat to this. We can't work in reverse and assume that this is going to be true if we negate everything. We can't say that, oh, well, does that mean if the limit is equal to 0 that we converge? And that's not necessarily true. In fact, no information about convergence or divergence can be obtained. It might converge, but it still might diverge. So I've got a couple of really quick problems that shouldn't take very long here for you to practice with the nth term test for divergence. And I'd like to set the timer here just to maybe 1 minute and have you kind of look through these while I take a sip of water, and we'll go through these solutions here. So see if you can use the nth term test for divergence and find out some information about these guys. Okay, now I know that was pretty quick. Working each one of these at a 15-second pace is a pretty tall order, but let's see how you're able to at least get through the first few. And I'll start by taking the limit as n approaches infinity of this expression, n over 2n plus 1. And we could use a variety of ways to solve this one. Probably my favorite, because we have our n approaching infinity, we could compare the degree of the value of n on the top and on the bottom. They both have exponents of 1. They match. So what that basically says is that we could divide by the coefficients. And this limit is going to be 1/2. We could also use L'Hopital's pretty quickly there. Now, because this limit is not equal to 0, right? Last time I checked, 1/2 is not equal to 0. Then we know that this is going to be a divergent series, right? If the limit is not 0, we know that we diverge. Now, if you take a look at 2, and I'll tell you what, I'm going to maybe think about 3 in the same light. They have very similar characteristics. In both cases, if we let n get as large as it wants to be, that's going to cause the denominators to get very large, right? Now in problem 3, the denominator is going to get larger faster. We kind of think, well, does that make a difference? Does that mean something? Down the road, it very well might. But in the case of this nth term test, we can see that both of these limits are going to be 0, which means that the nth term test doesn't apply, right? And I think what I'll just do for purposes is just say not applicable in A. Right? Now, we still might diverge, we still might converge, and some of you might know the answer to these because you've been exposed to it. But if you haven't been exposed to this is something that's going to be coming to you this week. In fact, one of those converges, one of those actually diverges. All right, now if you look at the last one here, for the limit of the natural log of n over n, this one's going to take a little bit more thinking because we have the issue of an indeterminate form. If we try to let n grow really fast, we get infinity on top of infinity. So that means that we're going to have to use L'Hopital's rule. Now, in the interest of time, I'm going to go ahead and just use L'Hopital's rule right from the very get-go. But whenever we use L'Hopital's rule in a free response format, it should be very important just that we talk about the conditions of L'Hopital's rule. So we should probably say that the limit of this numerator as n approaches infinity is going to approach infinity, and the limit of this denominator as n approaches infinity is going to approach infinity. Therefore, L'Hopital's rule is going to apply. But for the purpose of this video, I'm just going to go ahead and perform the L'Hopital's rule very quickly. And once again, we see that, well, we're going to get a 0 for this, right? And getting 0 is the worst thing that can possibly happen if you're going to use the nth term test. It just simply says, oh, darn shucks, we're just going to have to look at using another test. And I don't want to spend a lot of time with the graphs that I've made for these particular problems, but you can see here, these are in the documentation that you can download, and I will be using these graphs again later in the week. But remember our first particular one, the nth term expression that was n over 2n plus 1 in practice 1. Well, this shows you a nice graph of the sequence of terms, right? It certainly looks like an increasing sequence. It's kind of starting to level off a little bit. In fact, it looks like it's going to level off at 1/2, right? We're going to flatten the curve at 1/2. Well, that makes sense because we took the limit of this a moment ago to get 1/2. But we're now interested in graphing what the series would look like. All of those partial sums, if we were to take the value here, which is 1/3, and add the value here, which I believe is what, 2 over, when n is 2, you get 2 over 5, right? 0.4. And if we keep a running total of those particular items in graph, we're going to see this green curve. And it's very, very, very obvious, I hope, that this graph is just sort of going way up into the atmosphere to infinity. And that's why we could say that this diverges, right? We're not going to reach that finite value. Now, if we take a look at, let's take a look at that 1 over n squared, okay? Those are what the nth terms look like when we sketch. But if we were to sketch the partial sums, we don't quite get that moving way into infinity. We sort of get this leveling off, but are we really leveling off, or are we still increasing just at a very, very slow rate? So those are going to be questions that we're going to be able to address later on through the week. So for a debrief and summary here, we kind of wrap this up and look at the enduring understanding that we're trying to convey. It's just simply that we can see that applying limits may allow us to determine the finite sum of a group of infinitely many terms, right? It's still it's an idea that still to this day blows me away. You can add an infinite number of things and get a finite result. A couple of our key takeaways is that if we do sum the partial sums and get a finite value that we call S, then that means that that particular series will converge. And then our nth term test takeaway is that the summation of A sub n will diverge if the limit as n approaches infinity of a n is not equal to 0. Common errors, misconceptions, and pitfalls. Certainly you want to know the difference between between a term a sub n and a partial sum s sub n. It's very easy to get those two things confused. And then let's not forget that if the limit as n approaches infinity of a sub n does indeed equal 0, this does not necessarily mean that the series will converge. A different test may be required. Brian and I will be talking about those throughout the week. We got just a really short AP practice question here. It's not going to take a whole lot of your time. You can just take a look at these maybe before tomorrow, and perhaps Brian might address some of these. But it's just a way that you can maybe use this nth term test and practice just a little bit, because we know that you're a little limited on the number of tests that you might know, especially if this has been new to you, if you haven't been exposed to this before. Once again, we want to make sure that all students have access to the internet. So if you have a friend that you know is having a hard time, they want to access advanced placement, the channel here on YouTube Live, have them reach out to the College Board at cb.org/tech, and they will certainly steer you in the right direction. Last Friday, Brian had a great project for you guys to tweet out with the hashtag AP Teachers Rock, AP Students Rock. It's a way that we can sort of keep our community tight and really start to celebrate some of the wonderful things that are happening, because it's tough. This is tough for teachers. This is tough for students, and we want to make sure that that you're all understanding that we can get through this. And there are great teachers out there. There are great students out there. If you're watching this, you know that you're a great student by taking 45 minutes of your time to work on your calculus. And so a couple of feature tweets as far as the AP Teachers Rock is concerned is coming from a group of students that said, I want to give a huge shout out to my calc teacher, Mrs. P. Not only has she spent her time reviewing with us over this break, but she always asks if we need anything not related to math. She's a great teacher and a great person, and I'm sure that Brian and I would agree that students are very lucky to have her. On the side of AP Students Rock, we had several teachers to say that we're going to give a huge shout out to my AP Calculus students who are continuing to work and review all of our content, despite the fact that teachers aren't permitted to grade our activities. So surrounded with tenacity, you will rock the exam. So it's so great to see all these positive sentiments being sent in both sides of the classroom. Brian, I certainly believe that staying positive is of the utmost importance during this time. You'll never stop believing that you're among the best mathematicians in your schools. You're among the best high school mathematicians on this planet. If that were the case, you wouldn't be taking Calculus PC, and I'd be lying to you if I probably didn't have ulterior motives in wishing you success. Those of you out there watching, you're our future engineers. You're the engineers who are going to develop things that make all of our lives easier. Some of you may work in the business world. You're going to be the ones who are going to keep our economy growing for future generations, for my kids, my grandkids. Some of you may be healthcare professionals. I certainly can't say enough about how important the roles of these individuals are right now in our society as of late. And some of you may be scientists. Maybe you'll be working in a lab one day. Maybe you'll discover medicines, vaccines, and even cures for chronic illnesses and even infectious diseases, so that we may never have to deal with a situation like this again. You know, a famous AP Calculus teacher from Bolivia who taught in California said it best: "You are the true dreamers, and dreams accomplish wonderful things." So I want to thank you for watching. We know that Brian is going to come in tomorrow and give us a great lesson over alternating series. So we want to make sure that you do try to complete this practice question, and we'll be back with you tomorrow. And in the meantime, I'm going to enjoy a little slice of pizza. Enjoy your day. We'll see you next time.
Hello and welcome everybody to AP Calculus Live. Whether you're joining us live this morning or whether you're watching this as a recording later on, I'm so glad that you're here. And I'm looking forward to working with you today as we continue our discussion of series and this concept of convergence that Tony Record kind of got off to a jump start yesterday in our session. Today is day 5 of these AP Live YouTube sessions, and it got me thinking a little bit. As you come on these AP Live sessions, you see this sort of cover slide letting you know that number 1, you're in the right place. This is for Calculus BC, and number 2 is kind of giving you an overview of today's topic or today's lesson. But it's just sort of sitting there in silence. And I thought, you know, what we really need is some really cool theme music, right? Some intro song for Calculus BC, because it's cool in Calculus BC, right? And we can't use popular or well-known music because there's some marks and some copyrights and some things like that. And so I'm not allowed to play those, otherwise we booted off the air by YouTube's copyright censors. And I realized also I don't have any musical ability. Right? I was like, I'm gonna write this really cool song. I realized number 1, I can't sing. Number 2, I can't play any instruments. And number 3, I'm not very creative. But I realized we have very many of you out there who might be. So I realized my mission in life is my dream part of my bucket list is I need somebody with some musical abilities to put that creative juice into something productive and create a nice little 30 to 40 second jingle theme song intro for Calculus BC. So if that's you, I need one of those. I need to have one of those. That way each day we can get off to a jump start with some nice intro music to get our blood flowing before we jump into these big ideas of convergence and series. So I'm gonna throw that out there, and then hopefully my dream is sometime before May 1st we're gonna have our calculus jingle going on. So I'm gonna go through a couple of housekeeping items, and while I'm doing that, I'll remind you that all the materials that we're doing on these live sessions, you can find them in our Dropbox folder. And so when you go to the YouTube channel, just underneath the title, you're gonna see a little link right there. If you click on that link, it'll take you to a Dropbox, Isaac Newton's personal Dropbox, that he's sharing some information with you. And we'll get the handout. So all the problems that we're doing during these sessions, you can print them off in advance if you would like, and you can follow along with us if you have the ability to print. And then after each lesson, we're also going to upload the worked out solutions to each of those problems. So not only are you going to have an answer key, you're going to see some really step-by-step detailed solutions to help you understand not just what the answers are, but how we arrived at those answers. And as always, we have to give a shout out to our friend Ted Gott, because he is so generous, and each night he types up his keys for us so we can share them with all of you. So those will be in there following each of our sessions as well. In these sessions that we do, we're not going to be able to cover all of the problems in the session, so I purposely write some extra additional problems. That way, once we're done with these, if you're a teacher, you can sign up to your students for more practice, or if you're just a student doing these on your own, you've got several more examples that you can implement and try some more on and have the keys there for you. So you're welcome to print those off and use them as you go. It's the same exact link for every one of our videos. And so if you open that link, you're going to see a folder for each day, each topic, and you can print off the appropriate ones. So my name is Brian Passwater. If you are new, this is your first time, I've been doing these live sessions that are recorded that you can watch them later as well every day, and I'm co-teaching with a good friend of mine, Tony Record, and you see us kind of bounce back and forth between the two of us each day. And so that's kind of how we've been doing these. Once we get more toward the review sessions at the second half of April, we'll probably start doing some co-teaching or some co-presenting. But for right now, we are instructing kind of bouncing back and forth between us. That way you get some different voices and different insights and different approaches each day. I am a teacher at Speedway High School in Speedway, Indiana. This is a part of Indianapolis, the central part of Indiana. I teach calculus and pre-calculus there. I know I have a few of my own students that are probably watching today, although they're on spring break, so I did tell them to take a week off, reset themselves, regroup themselves, get some rest and relaxation from all this e-learning that we've been doing. And speaking of e-learning, we know that a lot of students and teachers alike, this has been a rough transition, right? We weren't really intending to have our last month and a half or 2 months before the AP exams be distance learning. And so we've had some obstacles and some barriers and some things that have been challenging. We've also seen a lot of resilience. We've seen a lot of teachers and students not use excuses or use these obstacles as a reason to not be successful. And so we wanted to give you guys a chance to tweet out some positives. And so we asked you on Friday to tweet out. So if you're a student, we asked you to tweet out about your teachers, your AP Calculus teacher or any AP teacher, and what you really appreciate, love, or admire about that teacher. And then if you're a teacher watching, we asked you to tweet out about your students. What do you appreciate or love about your AP Calculus students? And we asked you to include those hashtags AP Teachers Rock if you're a student, and use the hashtag AP Students Rock if you're a teacher. And then each day, Tony and I are going to read out a couple of the tweets that we thought were interesting and nice. So the first one today is going to be shout out to Mrs. S, my amazing calc teacher. Her love for math and sloths is contagious. I picked this one because I thought it was interesting that a teacher had such a love of sloths. That was pretty awesome. I miss her sarcastic jokes and appreciate the time that she took to get to know each one of her students. MHS loves you. Hashtag AP Teachers Rock. On the other side, from a teacher, a huge shout out to my AP Calculus students who are continuing to work and review all of our content, despite the fact that teachers aren't permitted to grade our activities. I'm so proud of your tenacity. You will rock the AP exam. So if you've got a great AP Calculus teacher or just any AP teacher, you've got some great AP students after our session today, take to Twitter and tweet out about it. Make sure you include the hashtags that I have here. That way we can find those, and then Tony will share a few of those tomorrow. We'll continue to do that each day to share some of the positive things that are going on during these e-learning days. A couple of the upcoming lessons that we're going to see today, as you can see on here, is April 1st. It just occurred to me, it's April 1st. Wow, we're April already. I can't believe that. It's almost like an April Fool's joke that we're in April. If I would have realized it was April, I would have made a cool April Fool's joke. I let you down. I apologize for that. But today we're looking at the alternating series test, and then later on this week we're looking at a couple of different tests for convergence, including the P-series, comparison, and geometric series. And then next week we're going to transition more into Taylor polynomials, the ratio test, and then alternating series, airbound of a Taylor polynomial. And then once we finish that next week, we're going to spend 3 entire weeks from April 13th until May 1st just getting you solely ready for the BC exam. I've been doing a lot of prep and review. We'll be reviewing all of the topics that are on the BC exam, including the earlier units that are part of the AB curriculum, as well as the integrated BC topics that we're going to see on this year. So Tony and I are really excited. There's a total of 28 of these lessons, right? Between what we're doing now plus the review, there's 28 of these. And Tony and I have talked at length about this. That if you can find a way to join and attend and practice during all 28 of these lessons, you're going to be as prepared as possible for whatever this exam looks like, right? Right now, I know that there's a lot of uncertainty. Calc has been able to release some information about the exam. We don't know all the details yet. We know that this Friday, April 3rd, Calc will release more information, hopefully to put our minds at ease about some of the logistics and question types that the exam is going to have this year. But even knowing that, we know it's going to be different. We know it's a different exam than we've ever seen before because of the fact that we're going to have a 45-minute test instead of our normal over 3-hour test. But we want to find ways to prepare for whatever we're throwing, right? I think the best way to prepare is just to do a lot of really good problems and then make sure that we understand a really deep conceptual understanding of each of these topics that we're covering. So if you can find a way to attend these 28 sessions, Tony and I will do our very best to make sure that you are ready for the exam and have all the success we've been working on this entire year. So today's warm-up, every day we have a warm-up, and the warm-up is just a follow-up of the AP exam question from the previous day. And so if you were watching Tony's session yesterday on topic 10.1, our introduction to convergence in series, this was the AP practice problem that he gave at the end of that lesson. And I would strongly encourage you, as you see these lessons, to always try that AP practice problem again. There are going to be some really good experiences and practices to reinforce the things that you've done. So the problem from yesterday that we're going to start off with is determine if possible if the given series diverges based off of the nth term test. And so Tony and I started talking about this the other day, and we started realizing you guys are in a lot of different places, right? Some of you have never even started series before. Your school got released before your school had a chance to even introduce topics, and maybe you've never seen series prior to calculus. Your pre-calculus class or algebra 2 class never got to to experiment with them or talk about them. So this is all completely brand new to you. Some of you maybe has done a little bit of series. You maybe started that in your calculus class before we had to go home and do some distance learning. So you've seen some of these topics, but you haven't gone through all of it. And some of you possibly have gone through the entire unit. You've actually finished all the series stuff. So you've seen all these things before. So all this is sort of review and refreshing for you. So I want to have you keep that in mind as we're doing this, especially if you've seen these topics before. Try to remember and only use the things that we're doing as we learn them, right? So trying to use things from the future that you've learned and try to base it off of just the things that we talked about. And so this particular question says, which of the following diverges based on the nth term test, right? So because the question says based on the nth term test, we're not allowed to use outside information. So even though some of you might recognize some of these series as things that you've learned as geometric, or later on you might know as a P-series or something else that we've seen, you might know that you use a ratio test or something else that you learned in unit 10. For today, all we know is the nth term test. And it's important to recognize that when the question's written, because the College Board sometimes will do that on a question. They'll ask you to do something very specifically. They'll name something out and use the nth term test. And when they name something out like that, you don't get to do it another way. You don't get to use your own method that you understand. They want to see specifically if you know how to use the nth term test in this case. So let's go ahead and take a look at these 2 problems and see if we can use the nth term test. And so I'm going to refresh our memory. This is what the nth term test says based on what Tony taught us yesterday, that the limit as n approaches infinity of a sub n, if that limit does not approach 0, then that means that our series, right, of a sub n diverges. That's what the nth term test says. And notice the nth term test has a condition, and the condition is the limit of a sub n does not approach 0. So whenever we have conditions, we don't get to invoke or come to a conclusion unless the condition is met. And think about this whole course, right? Think about this whole entire content from unit 1 all the way until now. We've had several different theorems that have conditions that we have to meet before we're allowed to apply those theorems or those tests, right? We have the intermediate value theorem, which only can be invoked if we can show that the function is continuous on a closed interval. We have the mean value theorem that we can only invoke or come to a conclusion so that the function is continuous on a closed interval and also differentiable on a given open interval, right? We have L'Hopital's rule, which is also a theorem that says we can only apply it if we can show the conditions that the limit of the numerator and the limit of the denominator are either both 0 or positive or negative infinity. So we have all these theorems that happen in mathematics, and it's important that we check for conditions before we try to apply them. And so the nth term test is no different. We have this condition. If this condition is not met, there's no conclusion that can be reached. So this theorem only works, this test only works if the limit does not approach 0. If the limit of a sub n does approach 0, then we can't use it. It doesn't mean that the negation is correct. It doesn't mean that the series converges. It simply means we can't use this test, and we're going to have to apply a different test. And so I think the nth term test is one of the most misused or misunderstood tests and misapplied tests because students assume if the opposite of the condition is true, that we know something about inclusion, and we simply do not. So we're going to see an example of that here in warm up. So in this first example, if we're going to apply the nth term test, we're going to take the limit as n approaches infinity of 5 to the n. Well, we can see previously that the limit of 5 to the n as n approaches infinity is just going to be infinity. And that does meet our condition. Our condition for the nth term test says if r does not equal 0, which it does not, then that means that our series diverges, and it's going to be by the nth term test. And notice how I wrote this out. I guess I should probably write all those there, right? Nth term test. I'm trying to skip some steps. I feel like this is one of the reasons why I can't even talk and write at the same time. So no wonder I don't have the ability to write a theme song for us. But notice the work I showed, right? You know that this year's exam is going to be unique, and that there aren't going to be any multiple choice questions. And so everything is going to be written out, right, or typed out. And so when we do this, it's important that we show not just our work, we show a really clear understanding and a really clear path of what we're thinking, right? When we're doing FRQ problems or open response problems, really our goal should be that our work is teaching somebody else or telling a story of what we're thinking, right? That what we're thinking and the path that we're taking, someone can see our work and tell a story to them, and that they can see all of our ideas and why we're doing what we're doing beyond just arriving at a simple answer. Part B, we have 2 in factorial over 1 minus 3 in factorial. Those little exclamation points are factorials, right? If you haven't done any series before, that might be actually a new symbol to you. And so just on the side here, I'm going to refresh or kind of instruct you a little bit about what we're talking about with factorials, because these are going to play a pretty big role in this unit as we move on. A factorial of a positive integer is just that positive integer, and then we're multiplying by each integer less than that number down to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1. In this case, I believe that would be 120. 3 factorial would be 3 times 2 times 1, which is 6. 1 factorial is obviously just going to be 1. And the one that usually throws some students off a little bit, and we do this by definition, meaning we define this, is 0 factorial doesn't really fit the rules. When we talk about factorials, we plug in positive integers to create a factorial. 0 is not a positive integer, but we do define 0 factorial to be 1. So we actually have 2 different factorials that both equal 1. And there's some pretty good reasons for that. By defining it to equal 1, it sort of makes the rest of the math make sense. It makes sense to make it 1. And it has to do with permutations, how we arrange things, and things like that. We're not going to get too in depth on why we make 0 factorial 1, but it's a good fact to kind of keep in the back of your mind. As we get more into factorials, we can elaborate on that more. So here we're doing this summation of 2 in factorial over 1 minus 3 in factorial. So applying the nth term test, we're taking the limit of 2 in factorial over 1 minus 3 in factorial as n approaches infinity, and that's going to be the limit as n approaches infinity. Remember, we're doing a limit at infinity, which means as we're trying to evaluate this is going to be equivalent to just 2 in factorial over negative 3 in factorial, right? We're only concerned about the most dominant part of the numerator and denominator. And in this case, those n factorials are going to cancel, and we just get negative 2/3 for our answer. Well, think about our nth term test. The condition is that the limit cannot equal 0. Guess but this does not equal 0. So the limit did converge in this case, but the key is it has to converge to 0, and this was not equal to 0. So according to the nth term test, that limit is not 0. And I know that this series diverges by the nth term test again, right? And so we have another series that diverges by the nth term test. So let's move down to C, and we're going to try the nth term test again. And in this case, I'm going to use some properties of exponents. That's going to be the key to this problem. It's kind of manipulate a little bit to make it something we can work with. And so 3 to the 1 minus n is just going to be 3 to the 1 power times 3 to the negative n, right? It's sometimes harder to break things up. But remember, these are equivalent, meaning if I said 3 to the 1 times 3 to the negative n, because those have the same base, base 3, we know we can add up their exponents, right? So I can combine that into 3 to the power 1 minus n. Well, the same thing works in reverse. If I have one base, I can split up the exponents like we did here. So I can do something simply with this 2. 2 to the 1 plus n is going to be 2 to the 1 times 2 to the n. And by doing this, now I can clean this limit up a little bit, and I can get, I have 3 to the first power times 2 to the first power. Well, that's going to give me a 6. And then I have 2 to the n, and then I have 3 to the negative n. So I'm going to bring that 3 to the negative down to the denominator and make it just 3 to the n. And then this gives me the limit as n approaches infinity of 6 times 2/3 to the n power. And now as I apply this limit, 2/3 to the infinity power is just going to be 0, right? And so we have the limit of this is 0. Well, if we go back to our nth term test requirements, we can only apply the nth term test if the limit is not equal to 0, right? And in this case, our limit does equal 0. And so what Tony was teaching us yesterday was, what can we say about that? Well, according to the nth term test gives us no information, right? So the nth term test gives no information about that series, right? We don't know about the series because the limit as an approach to infinity was 0. Like I mentioned earlier, if you've done some of these topics before, if you've covered the geometric series, and you could figure out that this series converges using the geometric series test, but specifically using the nth term test, we just simply don't know. So that was our warm up from yesterday, and we're going to tie that into kind of where we're going today, right? So this is our overview today. What we're going to do, well, we're going to solidify, we're going to deepen our understanding of these concepts of partial sums that Tony mentioned yesterday, as well as this idea of convergence and divergence. Those are pretty important big words that have a lot of meaning, and we talked about them pretty briefly yesterday, but they're going to keep coming back up. So I want to make sure that we really do understand what these words mean, so that way we don't get tricked or make some false steps on us with problems. And then hopefully we're going to be talking about how to understand and use the alternating series test when applicable. So what should you know for today to be successful? Well, the nth term test for divergence. Well, fortunately, that's what our warm up was about, so hopefully that was a good refresher for you. And then also how to evaluate a limit at infinity, which we did during the nth term test. So after our lesson today, what are you going to be able to do? Well, think about this question right here. There's 4 series given below. Which of these series can be shown to converge using the alternating series test, right? And notice again, the question wasn't which of these series converge, right? When somebody asks you which of these series converge, you've got the whole, your whole tool chest of tools that you can use to solve those. Anything that you know about convergence tests, you can use. But if a question in the AP exam asks you specifically about the alternating series test, you have to know that test well enough to know not just which series converge, but which series converge because of or by the alternating series test. And so we have 4 series there, and we learned that some of these converge, some of them don't. But more importantly, we want to know which ones meet the conditions of the alternating series test. So before we jump into the alternating series test, I want to take a look at some of the words that Tony described yesterday to kind of clarify and make sure we're on the same page, so we can see how these things work, right? And so we have this idea of a sequence, which we don't mention the word sequence very much in Calc BC, but that a sub n, that little expression, that formula for the terms of a series, that's a sequence, and a series is just adding up a sequence, right? So a series is adding up a set of numbers, a sequence, and that would give us a series. And what we're really concerned with in these next several sections are how do you tell if an infinite series converges or diverges? It's pretty remarkable, and Tony even mentioned this yesterday, which is we can add up an infinite amount of terms. We can add up infinitely many things and still have that total sum not get out of control, not go to infinity or negative. That you can add up infinitely many things and have that sum approach an actual value. And it's sort of mind-blowing on the surface about how that would work. And we're going to really discuss in these next several sections of how do we determine whether these things converge or not. And so one of the things that's pretty important is this idea of a partial sum. And I think a lot of times we kind of skim by this. We don't give it much credit or talk about it much. But I want to make sure that we understand the importance of this concept of a partial sum, because a partial sum really is the heart of whether a series converges or diverges, right? And so a partial sum is just adding up the first n terms of a series, right? So if I added up just the first number of a series, that would be the first partial sum. If I added up the first 2 numbers of a series, that would be the second partial sum, and on and on and on. And so and at the heart of what's happening here, a series will converge if those partial sums, right? Notice we have s sub n here, not a sub n. If the limit of those partial sums approaches L is a number, a real number. If the limit of partial sums approaches a number, then that means the series converges to that value. And if the limit of the partial sums does not approach a real number, that means the series diverges, right? And I think intuitively we kind of just assume or think that that value that it would approach to make it diverge would be like infinity or negative infinity. We always think, okay, the terms go to infinity, they're unbounded, or negative infinity, that would make the whole series diverge, which is true. But that's not the only way a series could diverge. You could diverge without ever approaching infinity or having unbounded behavior, and that would happen through some oscillating behavior. You might remember at the very beginning of the year we were covering limits in Calc AB, we learned some reasons of why limits would not exist, right? And one of those reasons was unbounded behavior. We're taking a limit of partial sums here, so one reason why it wouldn't exist is unbounded behavior, meaning is approaching infinity or negative infinity. Then another reason why a limit might not exist that we learned at the beginning of the year is by oscillating behavior, meaning the sums are just bouncing back and forth without actually approaching a value. They're not really getting closer to any real number, even though they're not getting out of control. They're just bouncing or oscillating back and forth. Either one of those cases of partial sums would create a divergent series. And so the nth term test, which Tony mentioned, I mentioned in the warm-up, is that the limit of a sub n does not approach 0. This is our condition, right? This condition, if that's true, and that tells us the series diverges. So let's take a look at a few examples. I want to look at these through partial sums. So again, I know that it covered a geometric series. That you might have seen these and done these this way, but I want to show you the value and sort of the power of partial sums. And so here we have the series of 1/2 to the n power. I even wrote out the first several terms there for you. It's always helpful, I think, to write out these terms because it gives you an idea of what's happening with the series. And so s sub 1 would represent the first partial sum, and the first partial sum is just the first term. It's just going to be 1/2. And then s sub 2 is going to be the first 2 terms added together. It's the second partial sum, so it'll be 1/2 plus 1/4. If we add those together with common denominators, we get 3/4. And then we get s sub 3, which is 1/2 plus 1/4 plus 1/8. It's the sum of the first 3 terms of the series, and that would give us 7/8. And then s sub 4, the fourth partial sum. I'm going to just do these first 4 so we can hopefully see a pattern of these partial sums. This is going to be 15/16. And we start to recognize maybe with these partial sums, our answers. Notice all of these denominators, right, were all powers of 2, and not just any power of 2, but the power of 2 of whatever partial sum we were working with, right? And so the nth partial sum, the denominator is just going to be 2 to the n power, just like the fourth partial sum was 2 to the fourth power. The third partial sum, the denominator was 2 to the third power. Yeah, this is going to be 2 to the second power, and then 2 to the first power. So the nth partial sum is just going to be 2 to the n power. And then notice the numerators for each of these partial sums is just 1 less than the denominator, right? And so the denominator is 2 to the n, and the numerator is just going to be 2 to the n, then minus 1, right? So 15 was 2 to the third minus 1. Sorry, 2 to the fourth would be a better idea, right? And then 7 is going to be 2 to the third minus 1. 3 was 2 squared minus 1, and then 1 was 2 to the first minus 1. And so this is our expression for the nth partial sum. This is sort of a unique problem because we actually come up with an expression for the nth partial sum. On most series problems that we deal with, we actually can't come up with an expression for it. It's always interesting to me because we tell students we want you to figure out whether these series converge or diverge, right? I want you to figure that out. And once we realize the series converges, your natural response should be, okay, great, I know it converges. It approaches some number. What does it approach? What is that number? What is that value of L that the series approaches? And most of the time, we have to respond with either we're not interested in knowing that right now, or we can't figure that out right now, or that's beyond the scope of this course right now. So we're really interested in knowing if these converge or diverge, but it's actually less common to find out what it converges to. This example was geometric, and that's really the only test on the BC exam that we can find out not only does it converge, but what does it converge to. And Tony will be showing us how to do that on Friday. And so since we can do that geometrically, we can actually figure out what it converges to, because we just talked about how a series will converge if the partial sums, if the limit as it approaches infinity converge, and 2 to the n minus 1 over 2 to the n as n goes to infinity is equal to 1. What that tells me is this series, if I add these terms up infinitely, would equal 1. Now on part B, these don't have the terms written out. Let's go ahead and write out the first couple of terms here. If n is 1, for example, negative 1 to the 1 is just going to be negative 1. Negative 1 to the second power is just going to be 1. Negative 1/3 to the third gives me negative 1. And we can see pretty quickly this pattern of alternating terms. And so s sub 1, the first partial sum is just the first term. That's negative 1. S sub 2, which is the first two terms, is negative 1 plus 1, which is 0. S sub 3, the first three terms, is negative 1 plus 1 minus 1, which takes me back to negative 1. S sub 4 is negative 1 plus 1 minus 1 plus 1, which takes me back to 0. And we're thinking, okay, well, what would the nth partial sum be? Well, it's not going to be quite as simple as we did for part A, right? However, we can recognize, hopefully, pretty easily that the limit of those partial sums, right? We're starting at negative 1, then it became 0, and then negative 1 and 0. It's just going to keep oscillating, isn't it, backwards? And so the limit of partial sums does not exist, right? Because there is no value that those numbers are getting closer to or those numbers are approaching. And so because those partial sums, the limit of partial sums does not exist, I know that this series has to diverge because the limit of the partial sums does not exist. Now, again, if you can think about this a couple other ways using the nth term test, right? Yesterday, we can confirm that, right? The nth term test says if the limit of terms does not approach 0, then the whole series diverges, and the limit of these terms do not approach 0. They bounce back and forth between negative 1, 1, negative 1, 1. So there's a lot of different ways we can think about this, but it converges nonetheless. If you print off the guide and you're going along with us, I'm going to leave C for you to try as a practice problem. And like I mentioned, the solutions to this are in that Dropbox folder, the worked out solutions, so you can check your answers with that one. So we're going to jump into this idea of an alternating series test. Before we do that, I want to sort of reiterate what we mean by the phrase alternating series, right? An alternating series is a series whose terms alternate in signs. The key is it has to alternate. So at some point, they have to go back and forth between positive, negative, positive, negative, positive, negative. It's not enough just to say there's some positive terms and some negative terms. It's not enough to say there's a pattern. So they can't be positive, positive, negative, negative, positive, positive, negative, negative. An alternating series has to switch every single term at some point. From that point on, we'll switch signs, positive, negative, positive, negative. So here's a couple of examples of alternating series. Part A, we can just see the first term is positive and the negative, positive, negative, positive, negative, it kind of bounces backward. Part B, this is a closed form, but a pretty common way to think about alternating series is this negative 1 to the n power. That's going to generate an alternating series, and we can confirm that by plugging in some of these values. I always think it's helpful when you have a series and you're not 100% sure how to deal with it. Plug in the values of n to write out the first few terms. You get a better feel of what the series looks like once expanded. And so if n is 0, n to the 0 is 1, and 0 plus 1 is 1 at the bottom. And if n is 1, you get negative 1 to the 1 power, which is going to be minus 1 over 2. And what's going to happen is each time we do this, we're going to realize that we get this alternating series right there. And Tony's going to talk more about this series tomorrow, because it actually has a special name that has a lot of important properties, not just in mathematics and series, but actually in the real world as well. C is another one. I'm going to leave that for you to expand. But I want to point out D, because this is sort of what I would call like the hidden alternating series. It doesn't look like it's alternating. Typically, when we think about alternating series, we look for that negative 1 to the n power. It's kind of like a giveaway. But here, cosine of pi n, if we plug in our values, we're starting at 2, right? That's going to become cosine of 2 pi over 2 factorial. Then it's going to become cosine of 3 pi over 3 factorial. Then cosine of 4 pi over 4 factorial. And we're going to continue that way, right? Well, if we evaluate these using our unit circle, we realize cosine of 2 pi is just 1, but cosine of 3 pi is negative 1, and then cosine of 4 pi is positive 1 again. And what we end up getting is this alternating series. And so you have to be careful with that cosine of pi n. They might sneak that in there, and you might not recognize it at first as being an alternating series, which is why it really shows that the usefulness if a series is closed or condensed like this, to plug in some values of n just so we get a better feel of what that series is doing. So now that we know what an alternating series is, here's the alternating series test. If we have an alternating series like negative 1 to the n times a sub n, or negative 1 to the n minus 1 times a sub n, we have two examples here because the first term could be positive or the first term could be negative. It doesn't matter which one comes first as long as it's alternating, right? And so an alternating series, if we know it's alternating, will converge. Notice it only says the word converge. It doesn't say the word diverge. The alternating series test is only for convergence. So if these two conditions, right, both of these conditions are met, then we know that this series will converge. If one or both of these series are not met, then we can't use the alternating series to say that it diverges. Typically, we'll be able to use a different test to check for divergence. So number one, if the limit of a sub n is 0, and number two, a sub n plus 1 is less than or equal to a sub n for all n greater than n, where n is an integer. Let me break this down for a second to make it a little more clear. This is a fancy way of saying at some point, it may not be the first term, it could be 3 or 4 terms in the series, but at some point in the series, every term is either less than or equal to the term before. So at some point, the terms start decreasing, right? And they don't increase anymore. So number one, the terms of a sub n have to approach 0. And 2, at some point along in the series, those terms start getting smaller and smaller and smaller, and they never start going up again, right? So that's what we're trying to find out. So if we can show those two things are true, then we know that the series converges, right? For an alternating series. It's only true, by the way, for an alternating series, not for any series in general. So let's do a couple of quick examples to put this into practice. I have here in the bottom right-hand corner this reference here for the alternating series test. And I want to give a shout out to my friend Tony, who presented yesterday. He'll be on here tomorrow. Tony and I work really closely on these lessons together. So you only see one of us each time, but every time we're giving a lesson, the other person is watching in the background, checking for mistakes, and helping out do these developments. So I love to write problems and questions. So I write a lot of the problems that Tony and I use. And Tony is incredible with creating really good, aesthetically pleasing notes and materials. And so Tony puts together my slideshow for me. So I sit in the problems that I want, and he creates these, and he has these really good ideas, make things look well organized, crisp, and clear. So he makes my life a lot easier and does things that there's no way I would be able to do on my own. So here on a little reference corner, we have this alternating series test. And so I want to see if this converges. We're going to check first of all if the limit of a sub n is 0, right? So I guess it would help to understand what a sub n is, right? A sub n is the square root of 1 over the square root of n plus 1. And so I need to figure out if the limit as n approaches infinity of 1 over the square root of n plus 1, that needs to approach 0. It's pretty clear. If I approach infinity for n, we're going to get 1 over infinity in the bottom, which does approach 0. So condition 1 is met. Notice how I'm writing these conditions out because this is going to be an all open-ended AP exam. So we have to physically check and show that we're checking these conditions. And the second condition is that a sub n plus 1 needs to be less than or equal to a sub n for all values at some point. And so one way that we can check this condition is just find what the a sub n plus 1 term is. We already wrote what a sub n is here. So a sub n plus 1 would just be plugging n plus 1 in for n, wouldn't it? So it would be a sub n plus 1 would be 1 over the square root of n plus 1 plus 1. So in this case, it would be the square root of n plus 2 in the denominator. And I want to know, is that less than or equal to the square root of n plus 1, 1 over n plus 1? Well, this is going to be less than this term if this denominator is always bigger than this denominator, which it is, right? As long as n is greater than or equal to 0, then 1 over the square root of n plus 2 is always going to be less than or equal to 1 over the square root of n plus 1. So this is a true statement. So I met both of my conditions. So I know that this converges by the alternating series test. So I left another example on here for you to try on your own. It would be example 3. And example 3 is a little bit more interesting because this is an example where it's not going to immediately decrease. So these terms are going to increase briefly before they start decreasing. So I'm going to let you try that one on your own. And again, don't forget these worked out solutions are on that link at the bottom of the video. You can see the step-by-step solutions that Mr. Ted got made for us. So I'll let you try that one on your own. And then this one right here, again, I just want to show you one of these problems. I like to write lots of problems that you haven't seen before. So I like to write some that are more basic, more kind of straightforward. You might see in a typical textbook or a classroom, but also give you some chances to see some things that maybe you haven't seen before to help you prepare for what the AP exam might do. And so I'm going to look at example B for a second. And here's why I want to look at example B, because if you're not careful, you're going to fall into a little bit of a trap here. The question is determine if the alternating series test can be applied. Well, this is a closed form. I mentioned earlier, it's good to plug in a couple of values, right, for n to see what this series looks like. And so if you plug in 1 for n, you get -1 to the 1 power, which is just -1. And then you get 5 times 1 minus 3. Well, that's going to end up giving you 2. If I plug in 2 for n, well, 2 times 2 minus 1 is 3. Well, -1 to the third power is still -1. And then 5 times 2 minus 3 is going to be 7. And what you're going to recognize, hopefully, is that every time you plug in a value for n, this exponent is always going to be an odd number, meaning -1 to any odd power is always going to end up being -1. And so these problems, it's not actually alternating. They're always negative. And so just because you see a -1 in the problem doesn't mean the whole series is going to be alternating automatically. So we want to be kind of cognizant and be careful for that. And that really illustrates the importance of writing out some of these terms. Now I'm going to go on a limb and guess that a lot of you haven't seen an example like D, where it does a piecewise function. So this is giving you a nice example where you can extend your understanding of alternating series and the alternating series test. Because a little bit of background on the AP exam is the College Board does what we call something called understanding by design, right? This is sort of how they develop the courses in their exams. And understanding by design is sort of some educational theory that says if we're going to truly understand, if kids understand something rather than just memorize and regurgitate, they're going to be able to display certain characteristics. And one of those characteristics is something called transferability. That if we teach you something, if you truly understand it, you can transfer that understanding, you can transfer your knowledge into situations that you haven't seen before. And this is why if you look at some old AP problems, sometimes you're like, where does this question even come from? How do they think about this? Well, they're trying to give you opportunities to apply what you know and transfer your knowledge into unique situations, because that's a really good way to assess whether or not you understand the material, or whether you just memorize a bunch of examples. And so by giving you examples you haven't seen before, it's giving you opportunities to practice that now. So that way, whenever the exam comes, whenever they throw at you, you've had experience with this, you've had a chance to practice the idea of transferring your skills to do this. And so I'm going to put a star by D. So I'd love to see you try that one. And I would do the same thing I did for B. See if you can write out what the terms are. And once you can write the terms out, you can figure out whether the alternating series test can apply or not. I realize at first it looks a little bit different and scary, but try it out and see what you can do, right? So what I would like you to try, I know it's about 9:45, so we're going to be wrapping it up in just a few minutes, but I want to give you a quick chance to look at one of the practice problems. I'm going to give you about 1 minute, and then we're going to wrap it up and look at the AP practice problem here and talk about what's coming up tomorrow. But take about 1 minute and see if you can apply what we did to this problem right here. And so here we're given a series, -1 to the n over 2n quantity factorial. And notice it says show. I'm not asking you that it can, or tell you it can. Show means yes, it should. To show me the steps. See if you can show those 2 steps that we talked about in order to prove that something converges using the alternating series test. So it's been about a minute, and we'll see if you got kind of on the right track or not. Hopefully you did. The 2 steps, don't forget, were number 1, showing the limit of a sub n approaches 0, and a sub n is the non-alternating part, right? So a sub n is the 1 over the 2n factorial. Well, the 1 over 2n factorial as n approaches infinity is clearly going to be 0. It's 1 over 2 infinity. And then the second part is, do the terms decrease? Is a sub n plus 1 less than or equal to a sub n? Well, if I plug in n plus 1 for n, it's 2 times the quantity n plus 1, or 2n plus 2 factorial is less than or equal to 2n factorial. Well, that is certainly true for any values where n is greater than or equal to 0, because it's going to be a bigger number factorial. As we saw those before, the bigger number factorial, once you get beyond 0, those numbers are going to end up being bigger and bigger and bigger, which means the reciprocal of that 1 over 2 plus 2 factorial is less than or equal to this. So this does in fact converge. This does converge. And a little bit of foreshadowing. Not only does this converge, this actually equals the cosine of 1. This is the cosine formula for a Taylor series. And this is something that was kind of taken away from this year's exam, but oh so important and oh so powerful. That you ever wonder, how does your calculator compute sine and cosine and things like that? It uses series like this, and it can add up terms. And so one of the things that we're going to be doing later next week is, how do you know how accurate it is, right? We can't add up obviously every single term forever. If I add up the first 4 or the first 5 terms, that gives me a good approximation. How close is that to the true answer of cosine of 1? So we're looking at that as well. This is also going to tie into our AP problem today. There's also a nice little card sort you can try on the handouts, where it gives you a series of 6 tests, and you're going to kind of categorize them up. For these 6 tests, could we apply the alternating series test as a converge, or can we not apply it? Is one of those conditions broken, meaning either 1, maybe it's not alternate at all, or B, maybe the terms don't approach 0, or C, there's no point in time where the terms strictly start to decrease for all n values. So you'll be able to try those out again, and the key is going to be uploaded for you to check as well. So it's a good little check for understanding there. And then another thing that I can see, especially on this year's exam, since we're having an all-written exam, is going to be a lot of explanations, interpretations, and justifications. Right? That's going to be a really big part of the exam. That's always a big part of the FRQs. So to really get to the heart of, you really understand these theorems. There's so many little twists and turns and nuances. It's easy to apply something that's basic form. It's a lot more tricky to look at it on a more conceptual level, especially if you don't have any numbers involved or any actual examples you can work with. So here's 4 statements. I would highly encourage you to try some of these as well. There's 4 statements, and each one has something false in it. Each one is a false statement. And so I want you to figure out what's not quite right about each statement, and then correct it. What do we have to change or alter to make those true? And so some of them might be a little more obvious, but some of these are really quite nuanced, and they're really going to get to the heart of your conceptual understanding of ideas beyond just you can memorize and apply a test. Okay? So let's talk about what we did today as we wrap up, right? Today, our enduring understanding, the big idea that we're trying to build towards in this whole unit actually, is applying limits. Using limits can help us determine a finite sum of infinitely many terms, meaning we can use limit ideas of partial sums in this case to figure out whether a series converges or not. And our key takeaway is this alternating series test. Remember, there's 2 conditions to that. And a couple of things to be careful with, that our alternating series test is for convergence, right? We would never say this diverges by the alternating series test. It only converges, right? And that first condition, by the way, right? Our first condition was the limit of a sub n has to equal 0. That's our first condition. Well, if that fails, then we know the series diverges not by the alternating series test, but by the nth term test for divergence, right? Any series to have any chance to converge. What Tony told us yesterday was a sub n, those terms have to approach 0. That's a requirement to any chance. If those terms do not approach 0, then automatically the series diverges. And so be careful, the alternating series test is only a convergence. If it fails, we're going to have to find a way that it converges or diverges to a different method. And then for any series, if the terms do not approach 0, we know for certain the series diverges. Okay? And then here's your AP exam practice problem. I'm going to be honest with you. I had a lot of fun writing this problem, and I'm kind of throwing the gauntlet down at you. So take some time to try this problem. It's a little tricky at first, but it's going back to that example problem I did earlier with the cosine problem. So consider this alternating series there where x is some value, x to the 2n over 2n factorial. And then part A, show that it converges when x is 3. So a little bit of a hint. We showed it converged earlier when x was 1. That was the example that we did. When x was 1, we showed it converged. Try the same idea when x is 3. And then B, if you can do that, show that it would converge no matter what number you plugged in for x. Right? So we can extend this to the general case that would converge for all values. And then finally part C, throwing in some things from earlier in the year, right? We're making some connect between different units and topics. This exam is going to make us do that. Consider a function f of x, where f prime of x, right, the derivative equals, I even gave you the first several terms there, right, the expanded form, where x, where f prime of x equals 1 minus x squared over 2, and it kind of goes on and on. Determine if f has a relative minimum, relative maximum, or neither at x equals 0, and give a reason for your answer. So believe it or not, whether you covered series or not, you have the ability to answer 3 of those problems right now. Teachers who are watching this, or students who maybe have looked at ahead of us and stuff, you might have recognized this looks a lot like the second part of Unit 10. We get a Taylor series and the Florence series and power series. But it turns out if we understand what we learned today and yesterday, we can actually solve these problems without ever having seen any of those things. So it'll be a really good test of our understanding and stretch. And Tony will start us off tomorrow by walking us through those solutions. So take some time and try those problems and struggle a little bit and try something and see how you did tomorrow when Tony comes back. A couple of quick announcements. We're going to have this on every single one of our sessions because it is so important. The College Board wants to make sure everyone has the tools they need to be successful on the exam and have access to the resources we're providing now, as well as access to taking those online exams when the exams come around. So if you know somebody who maybe doesn't have access to this or has issues with technology, please go to this website, cb.org/tech, and fill that out. That way the College Board can make sure they work with you to get you what you need. The College Board is extremely dedicated and passionate about giving all students the access that they need to earn the credits or have a chance to earn the credits they've worked for. And I'm going to leave this up here because Tony brought this up yesterday. I thought it was such a good quote by Jaime Escalante that said, "You are the true dreamers and dreams accomplish one thing." I couldn't have said it any better than what Tony did yesterday. Tony and I feel like you are all our honorary students, right? We teach our own kids. We feel like this next month and a half, our classrooms have been expanded, and we couldn't be more proud to call ourselves your teachers and helping you along this way. And we feel like it's our honor to work with you and to be a part of this journey with you. And so we hope sincerely that each day that you feel like you're getting something from these sessions, that you're getting better toward the exams. We're looking forward to all the success that you're going to have when the exams come. So thank you guys so much for watching us today. Don't forget to tune in live tomorrow. Tony's going to have an amazing lesson tomorrow over the P series with a little bit of absolute versus conditional convergence, which will tie into the alternating series test that we did today. So have a great day. We'll see you tomorrow morning.
Calculus, data polynomials, infinite series, differential equation, calculus, data polynomials, infinite series.
Calculus, Taylor Polynomials, Infinite Series. What a treat. Special thanks to Kate Yetman. Kate Yetman was sort of our chosen author of the music that we decided to go with this particular morning. And Kate's the daughter of Chris Yetman, who provided the wonderful vocal stylings on that particular track. Chris is a terrific teacher, a very prominent member of the AP Calculus, AP and BC community. So Chris, we thank you and your daughter Kate for that wonderful music. And we're going to try our best to feature some of the special talents that a lot of our viewers have shared with us. And we got a lot of them. We can make a whole album. So look for that to drop soon. The AP Calculus BC album comes on Music Store You. So I thought what we'll do today, something a little different because in this time of social isolation, I figured that a lot of music artists are out there kind of sharing their talents a little bit, kind of doing their thing. So I figured instead of learning calculus today, we're going to play some music all day long here for at least the first 45 minutes. So we're going to take some requests. Just drop them in the Twitter, and we'll be sure to get to them. Wait, our viewer count's going down. No, go away. Come back. No, we'll go back to calculus, I promise. Yeah, let's go ahead and do that. We'll hold that music off for another time. But I tell you what, we are going to bring the guitar back into this lesson because there's a really neat connection between what we're going to talk about today and music. So make sure you stick around for that. Today's lesson is going to primarily deal with 10.5 in the CD. That's the Harmonic Series and P Series. And the idea of these two types of series is going to be featured on this year's AP exam. And then I'll also piggyback on Brian's excellent lesson yesterday about alternating series. And we're going to discuss this idea of how to determine absolute versus conditional convergence. Okay, so that's the agenda for today. Once again, if you want to get a hold of any of the materials that we're using for our sessions, you can just go down into the comments underneath the video, access our Dropbox, and within the folder for the day, you can access the PDF file. Once again, my name is Tony Record. I'm a calculus teacher at Avon High School in Avon, Indiana, just west of Indianapolis here in the good old Midwest. And as you can probably tell, Brian and I are kind of battling a little bit of issues. Some seasonal allergies are upon us. I've got a little bit of warm weather, so we're kind of fighting through that, but we'll make it just fine. So upcoming lessons. Yes, today is April 1st, and that was my April Fool's joke, right? Not a very good April joke, I suppose. You guys knew I was going to be funny all day, right? You knew that. So we've got our Harmonic Series and P Series today. I do have the dates correct finally here. Thursday, April 2nd. Tomorrow, Brian's going to come back on with comparison tests, Convergence, and I'll wrap up the week Friday with a geometric series. And as you can see, we got a lot of fun stuff coming up the week ahead. It's going to kind of ease into the idea of Taylor Approximations, Polynomials, and then boy, when we get to April 13th, that's when all the great stuff is going to happen with the BC Calculus review that Brian and I have planned for you. So make sure that you plan for that. Now, to start with this warm up, I guess I'm not the only bearer of April Fool's jokes because I think Brian had the ultimate April Fool's joke on me. He certainly gave us a doozy of a warm up, and he left it on my lap to kind of pick up the pieces. But I want to tell you, this is an excellent problem. It's very well written, but I think what this problem sort of focuses on is not so much the calculus that we learned and how we can use that to solve it, but it sort of opens the door for us to maybe investigate and think about, are there better ways that we can actually answer some of these questions? And the answer to that is yes. So Brian kind of purposely put this on my lap here as his April Fool's joke for mixing up all those dates on him yesterday. So he got me. So anyhow, for this particular warm up, we have this alternating series, as you can all see, and we are asked in part A to use this alternating series to test to show that the series will converge when x is 3. So the very first thing that we might consider doing is saying, okay, let's take a look at what does the series look like when x is 3, and we do that, and we got something that looks like this. We just replace the x with 3. So we don't have this power series anymore, right? That has this variable of x. We haven't really talked to you guys about power series. We have this sort of normal, well-behaved alternating series. Now, I'm going to show you a slightly different solution than what is probably available on the Dropbox. Our amazing partner Ted did a fantastic job working through a very analytic way to solve this particular warm-up or this AP practice problem from yesterday. I'm going to take maybe a little bit more of an intuitive approach, maybe talk about why we would probably yearn for another kind of procedure that might make this job a little bit easier. And in my intuitive approach, I can use just a little bit of technology to kind of tie in some ideas together. But the very first thing that we want to do, if we're using the alternating series test, is determine what the limit is of the non-alternating component as n approaches infinity. So we take a look at that limit, let n approach infinity, and the non-alternating component, basically, it kind of does away with that -1 to the n. Now, we don't want to forget that he's there because he's obviously part of the problem, but we don't focus in on him when we take this limit in the first step of the alternating series test. And we get something like this. And it's sort of a sad situation when we have a factorial involved in a limit. In fact, it's kind of a sad situation when we have factorials involved in calculus in general because factorials just don't play very nicely with calculus. It's very difficult to take derivatives of them. It's very difficult to take integrals of them. So we have to think about this a little bit more intuitively. And if we do let n approach infinity, it's very clear that we're going to get a very large number on the top. We're going to get a very large number in the denominator. You might think, oh, that allows L'Hopital's rule to be used, but again, we can't take a derivative of something that contains a factorial. So one way to think about this, the idea of the partial sums, kind of, as we move into part 2, we can certainly think about the partial sum. But as far as this limit is concerned, we don't have that to rely on, so we just have to understand the magnitude of these numbers. So if I kind of move over here to just a listen spreadsheet, this is on the TI Inspire, but this is something that can be done on Excel. It could be done on any kind of calculator if you just push the right buttons in the right sequence and so forth. But I just made a little spreadsheet that allows me to enter some value for n, and I can kind of compare what 3 raised to the 2n is going to become, and then I can compare what 2 times n quantity factorial is going to be. And as we see at the very beginning, the 3 to the 2n, right, which is in column B, that's the numerator, is a little bit bigger, and then it becomes even bigger still. And then all of a sudden, 2 times n factorial begins to catch up a little bit, and then by the time we get n to be 4, 2n quantity factorial is really kicking the other guy's rear end, right? So we keep going on, and we find out that this 2n factorial is much bigger all the way through the problem. So if we continue, if we go back to this, we can kind of deduce that this denominator is growing much faster than the numerator, and that's going to give us enough evidence to say that this is going to be equal to 0. If we take a look at the second phase, or the second part of the alternating series test, what we're looking at doing now is showing that the n plus 1 term is possibly less than or equal to the nth term. We're questioning whether there's truth to that. So we would replace each of these n's with n plus 1. Now notice I will have to distribute the 2 in both instances. So I have 3 raised to the 2n plus 2 over quantity 2n plus 2 factorial. And I'm questioning whether that is less than or equal to 3 to the 2n over quantity 2n factorial. So with this, we do a little bit of manipulation. Let's say I divide both sides by 3 raised to the 2n. And in doing so, I'm going to reduce a bit. 3 to the 2n plus 2 over 3 to the 2n produce 3 squared, or 9 on the left side. Keep the inequality symbol there. And then if I multiply 2n plus 2 factorial to the right, and I think what I'm going to do off to the side here, I know sometimes students that I work with kind of struggle with this idea just initially, and then once they see it a couple of times, it begins to make sense. But when you have these magnitudes of these factorials in a quotient like this, we can construe the fact that this 2n plus 2 factorial is really the same as 2n plus 2 times the next number beneath it, or less than 2n plus 1, times the next value, one integer value below, which is 2n. And then all of a sudden, if I keep going downward, I can just throw my factorial there, and that's really what 2n plus 2 factorial is equivalent to. And then you can see some cancellation, and then you're left with 2n plus 2 times 2n plus 1. And if I go ahead and expand that, I get something that looks like this. And if I want to investigate this a little bit more, if I want to maybe set this inequality equal to 0, I can subtract the 9 over, and it looks like I got this. Right? I just kind of flipped it around to have all the variable expressions on the left side. And we have to think about, okay, well, is there going to be a value in where this statement is going to be true all the time from that point forward? And the answer is yes. It doesn't take a very large n to make this work. And just to kind of show you graphically, I've sketched that particular quadratic. Now note, I have to use the variable x just to appease the calculator, but this does graph this parabola that does have some portions of it that lie below the x-axis. But by the time we get to the n equal 1, we can see that we are well above the x-axis, and that's never going to change, right? We want to ensure that we have a position where a value, I should say, where this graph is always going to be above that x-axis and never change. So we've deduced here that the alternating says that the alternating series test does show that this particular series does converge. Now for part B, show that the series converges for all x. Now this is where we're kind of slipping into something that is very powerful, and I think Brian may have already mentioned how this is a very, very popular Taylor series that normally would be a big focus point on the AP exam, but in 2020 it won't be. But it's nice to kind of investigate that, and then we can revisit this idea a little bit next week when we get into our Taylor polynomial discussion. So in this particular case, we're going to leave this x as an x. So that means our first step would look something like this. We're going to take the limit as n approaches infinity of the nth term without the alternating component. So that would look something like this. Now because I don't know what the value of x is, I can't, set up some kind of a spreadsheet to kind of do this a little bit more intuitively. But instead I have to think about what I learned from before. And what we learned from before is that factorials are pretty darn powerful. If you take a look at sort of the pecking order, if you have something like x to the second power, we know that if we were to take an exponential version, right, x to some n power, that's probably going to be something that's going to grow a lot faster for most given integer x's when we have an n exponent than just say a squared exponent. But if we were to even apply something like a factorial, then we can probably consider that this is going to grow even faster, as we just indicated. So we have this sort of hierarchy of how things can grow. And there is a test, fortunately, there's a test, and we're going to share that with you next week, that will make, kind of considering how the convergence of a series that might look like this can be done a lot faster, and it's called the ratio test. So in this particular case, we know that that denominator is going to grow pretty darn fast, so we're going to go ahead and call him 0. And then for the second part, well, the second part's kind of interesting here, because we're going to do the same thing that we did up here for part 2, but instead of these 3's being located in that particular inequality, we're going to replace those with x's. So what that's going to basically result in is instead of having this 9 over here, we would have x squared over there. And then the right side is going to be the same as it was before. Okay? Now we're still sort of questioning whether that's true, right? So if we try to set this inequality equal to 0, it's a little strange, right? Now, I'm not saying that this can't be solved analytically. I think our answer key Ted does a fantastic job of walking you through that, and I certainly would encourage you guys to take a peek at that. But there's a way that this can be addressed in a visual fashion. I'm going to try to do this the best way that I can by looking at yet another graph. And so let me kind of show you what's going on here. This particular graph here is depicting the traditional 4n squared plus 6n plus 2, right? That's what we had normally with that polynomial expansion. But now I'm subtracting that x squared, and I had to call that x1 for the purpose of the calculator here. Remember, these x's are kind of like our n's. Well, I attached a slider, which is something that you can do with a variety of programs, Desmos, TI, Inspire. And if we allow that x1 to be virtually anything, right? There's the 3 that it was before in part A. But if we keep doing that, we find out that we still have this parabola. This parabola is still going to be fairly well behaved, and that as soon as it gets to a certain value here for n, it is going to reside above the x-axis and never change. And that's what that particular second criteria said. At some point, you have to be positive and not change your mind, and that's what we got. So we can say, because of that, this is a true statement, and we are therefore convergent. Now, part C might look like it's a little bit more complicated because it's kind of drawing upon some very old ideas, but it's not that bad because you've got this function f of x where f prime is now defined as that particular alternating series. And I've got it written in both closed form and open form here. It says determine if f of x has a relative minimum, a relative max, or neither at x equals 0, and give a reason for your answer. Well, we know that in order to have a relative max or min, we first of all have to establish that we have critical value, right? And that critical value is determined, let's use green here, is determined by taking that derivative and setting it equal to 0. Now remember, as we set this derivative equal to 0, we have to know what the x value is going to be, right? In this particular problem, we know that we're dealing with an x that's equal to 0. So we're trying to figure out, well, when does f prime of 0 equal 0, and then we can go on from there. So if we look at our f prime of x open form, we can just replace all of those x's with 0, and it doesn't take very long for me to figure out that, whoa, a lot of these things are going to go away, aren't they? In fact, every single term after that first term of 1 is going to disappear on us. So f prime of 0 is equal to 1. Now let's think about that. Well, what did we just say? The derivative evaluated at the point that we're trying to determine whether there's a max or a min is equal to 1. It's not equal to 0. It's not undefined. It's equal to 1, which means we don't have a critical number there, which means there's neither a max nor a min. So there wasn't a whole lot to that, but it was nice that this problem kind of drew upon some information that was taught very, very early in the course. All right, so let's go ahead and take a look at what's going to be on tap for today. And in this lesson, we are going to introduce a very important and quite common series. It's called the P series. And then we're going to determine the conditions in which a P series will converge or diverge. And then to kind of piggyback on what Brian did yesterday, I'm going to explain the difference between conditional convergence and absolute convergence, and sort of bring in this idea of the alternating series back in. What you should already know coming into today, well, by now hopefully we have a pretty solid understanding of what it means to converge and what it means to diverge. Those words get thrown around all the time this week and next week as well. And we want to make sure that we are fairly comfortable with techniques for evaluating limits. And of course, the alternating series test for convergence that we learned yesterday comes into play quite a bit. So an example of what you might see in a lesson or a problem set that deals with this particular concept or group of concepts would be, say, a summation from 1 to infinity of the sine of 2n minus 1 times pi over 2 all over n. The question would be, does this series conditionally converge, absolutely converge, or diverge? So that's going to be one of the kinds of questions that we address here in a moment. All right, to get us started, real quick recap on the alternating series. Let's refresh back. Each of these following series, as you can see, can easily be shown to converge because they meet the conditions of the alternating series test. Okay. Now that first example that we did, very difficult problem. I don't want you to worry about, especially when you look at the key and you see Ted's wonderful analytical approach. It's very likely that that's something that you're not going to do on the AP exam this year, or perhaps any other year. A lot lot of those things are showing proofs of some of the items that we're going to potentially expose you to next week. But as far as something like this is a little bit more rudimentary type of alternating series where each one of these is going to converge. And the reason is because whether I take the limit of the first one, the middle one, or the last one, they all have something in common. And if I remove the alternating component, let's say I look at the first one, that limit is certainly going to be equal to 0, right? If I throw in a square root, it doesn't really change the fact that that's going to also equal 0. Or if I were to square that in, it's just going to go to 0 even faster. So you can see that the first criteria of the alternating series test passes pretty quickly, pretty easily. The second criteria is just a matter of determining whether or not the first term, or I'm sorry, the n plus 1 term, my mistake, is less than or equal to the nth term. And without going through all the motions, because you saw it with the first warm-up, you can see that each one of these is going to behave that way. Each one of these is essentially what is a decreasing series in this particular instance. So these are very quickly recognized as converging by the alternating series test. But it kind of makes you wonder, are they converging because they're alternating, or is there something else that's going on with this? So we're going to get back to that here in just a second. But first, let's go ahead and take care of the initial concept for this particular topic, 10.5, and that's the convergence of P series. And if you read through this, and if it seems pretty easy, you're thinking it correctly, because this probably is one of the easiest, if not the easiest, test for all of the convergence series. There's about 10 convergence tests that a student would typically need to know in a PC class. This year things are a little different. You need to be responsible for about 4 of those 10, and this is probably going to be the easiest. A P series is pretty easily recognized because you got this 1 over n to the P form. You might have to do some simplifying to get it there first, and then we just simply take a look at that P. And if that value of P is strictly greater than 1, we know that that series is going to be convergent. That's it. Nothing else you have to do. If that P happens to equal 1 or be less than 1, then we know that that series is going to diverge. And I know that we say we have this extra little restriction here that P is always going to be at least greater than 0. And I think the reason for that is it's fairly trivial if we were to let P be some negative number, because if that was the case, this n to the negative P would have popped up to the numerator, and of course we don't have any chance to converge at all if we're just adding a series of unbounded numbers like that. So we're going to say that the divergence is going to be for P between 0 and 1, including the 1. So how would you tackle some problems that deal with P series? Well, really, if you can identify that P, that's about the only thing that you really need to focus on. So here it says determine the following series if they converge or diverge, and identify any values of P. So if we take a look at this first one, you could certainly rewrite this if you had a difficult time determining what the P was. So you would have to understand your rules for your exponents and your indices and so forth. So the cube root of n is nothing more than n to the 1/3 located there in the denominator, right? We want to keep that thing in the denominator. So we look at that and we think, okay, what is the P value? Well, P is obviously equal to 1/3. And because P is equal to 1/3, we know that this will diverge. And if you want to be even more specific, more precise about this, you could say this diverges because the P value was between 0 and 1. Okay, it's that simple. P series, piece of cake. Let's look at one more of these. I don't think we need to do all 5. I would certainly love for you guys to take a look at the 3 that we don't do, just to get some extra practice on your own. And you can always check it with the key that's posted online. So if you take a look at C, we've got in this particular problem a little bit of work to do because we don't quite have this written in the form that we would like. So if we take this into the -2 times n to the 1/2, essentially that would just be into the, well, -2 plus a half would be -3/2. And then we can rewrite this so that it looks more like what our P series is supposed to look like by plopping that into the 3/2 into the denominator, giving it a positive exponent. And then we look at that and say, well, wait, 3/2, that's certainly larger than 1, right? So identify our P as 3/2. So based on that, we can say that this series is going to converge. And the reason is because the P value is strictly greater than 1. All right. Now let's focus our attention a little bit to this topic in 10.9, which is, like I said, it's a really wonderful extension to what Ryan was talking about yesterday. We're going to define what it means to be absolutely and conditionally convergent. So one thing I want to make sure that you're aware of, we are dealing with for the most part, an alternating series here, but we could apply this in some other instances. So let's take a look at the summation A sub n. The summation is absolutely convergent, right? So it's the best kind of convergence that we have if the summation of the absolute value of that expression converges. Okay. Now on the other hand, we have the summation that is conditionally convergent if the summation itself converges, but the summation of the absolute value diverges. I know that can be very confusing. You get 2 different pieces of this, and when we solve some of the problems, I'm going to try to break it down and really give you a step-by-step process so that you can't get lost in this particular solution. So as we said before from the previous lesson on alternating series tests, we noticed that if a series does alternate, then sometimes it seems like it has an easier chance of converging. And the reason is because you're adding some positive number and then you're taking away something, which tends to make you a little smaller, right? And then we add something else and then we take away something else. So the potential to converge is there. But when working with an alternating series, we have those both positive and negative terms, and it's kind of natural to wonder, does the series converge because it was alternating, or would it have converged regardless of the alternating component? So if we consider this alternating series from the beginning of the lesson, right, the summation -1 to the n plus 1 over n, we've already determined that the series converges by the alternating series test. Right? We know that it satisfies criteria 1 and it satisfies criteria 2. But would the series still converge if it were not alternating? Well, we certainly know the answer to that because we just talked about P series, and it turns out that this guy right here is a very special version of the P series, right, where the P value is 1. And if you remember, I'll walk you back here just really quickly. The P series says that we will diverge if the P value is equal to 1. So we seem to have a bit of a conflict here. It's interesting that this guy will diverge, but we know that this guy up here converges. All it took was to add that alternating piece, and we have this different behavior. And when that happens, we have to sort of temper that convergence and call it conditional convergence. And we could spend a whole lesson talking about, well, really, what's one of the differences between something that converges conditionally and absolutely? But one of the things is that you could violate a very important rule in mathematics called the commutative property. In other words, I could take all of the terms, right, all of the individual components that make up that series, add them together, and get some results. But then if I take those same terms, put them in a different order, and add them up again, I get something different, which that's ludicrous, right? We know that 2 plus 3 and 3 plus 2 is always 5, but that doesn't always happen in the world of the alternating series. And because of that, we have this sort of tempered way that we think of convergence. So what this is saying, once again, is that the alternating series, -1 to the n plus 1 over n, is conditionally convergent because that alternating series itself converges. But if we took these series and focused on the absolute value of that nth term expression, we have something that diverges. And those two series are important to have very special names. And we're going to call the summation of 1 over n the harmonic series. That's what P is 1. And then obviously we have his friend, his alternating counterpart, the alternating harmonic series. And there in the green box, we have just a special sort of homage to that harmonic series. And if you hear and see the word harmonic, you might kind of think, well, that kind of sounds familiar, especially for those of you that are into music. A lot of my students, I'd say half of my students at my school are involved in music in some way or another, whether it's band or orchestra, or they just play music on their own. And I don't know if you ever stop to think about this, but how does the harmonic series have a relationship between harmonies in music? And it certainly has a very nice relationship. And it turns out that I happen to have my guitar here, so maybe I can kind of share this with you and see what this looks like. So here we go, the harmonic series. Well, one of the ways to think about this is on a stringed instrument like the guitar, we have these things called frets. And if I take the guitar in standard tuning, that's an E string, there's a fret right here. It's called the 12th fret. Right? If I count 1, 2, 3, 4 all the way as well, that's always funny. I tease my students that play violin, viola, cello, and bass that you guys are the real musicians because you don't have frets, right? Guitar players like me, we're kind of dumb. We have to have these little frets in order to our fingers. But if I put my finger right here, what I have is basically a fret position that takes this string and cuts it in half, right? The string is sort of mounted right here at what's called the nut, and right here that's called the bridge or the saddle. And right here, the 12th fret is half the distance. What does that mean? Well, that means that's an important note. And it turns out for those of you that play stringed instruments, you might know that this note is an octave higher at the 12th fret. Now we can apply that a little bit differently. Let's say I fret at the 3rd position, right? That would make, in other words, the string a third as long as it is. Well, that means I have to really kind of count a little bit farther. 13, 14, 15, 16. It's actually here at the 17th fret. And because this is an acoustic guitar, even though it's got cutaway, it's kind of hard to play really high up on the net, right? I have to get one of my electric guitars to do that. But right here, I have have a third of the length of the string as opposed to the entire length. Now, what I want to do with this is kind of change this. So this is now at the 17th fret. If I go 12 frets this way, I would be back here at the 7th fret, let's say, right? So at the 7th fret, I now have 2/3 the string that's being played, 1/3 that's being muted. What's the big deal here at the 7th fret? Well, this happens to be a B note, and I can find this B note a lot of different places on the guitar. One of them is right here on the A string at the 2nd fret. Notice these are essentially the same note. Now, where's this all going? That's where harmonies come into play. These two notes would be in harmony. They sound pretty good together. And in music, we call it a fifth. Right? Now, I'm not going to go into a long music theory lesson about the circle of fifths, but that's a pretty good note. And fifths are nice chords to play because they make a lot of good rock songs, right? So there's your little music lesson for the day, and we're not going to do much more. Yeah, we're not going to play that. So hopefully for those of you who have an interest in music, you can see that there's a nice connection between calculus and things in the music world. And the nice thing is that the history of math is so intriguing, and I really would encourage you guys to investigate some of these stories. And you can find them probably on the internet somewhere if you can get to a reliable source. But it's really interesting when you think about the person who first connected the idea of like a harmonic series to music, and it's not the person that you probably would attribute this to, but it was Pythagoras. Was one of the first people to make that connection. And we're talking about somebody who did all of his mathematics 500 BC. Now I doubt Pythagoras had a really cool tailored guitar around, but they had other kinds of string instruments like lutes and maybe the precursors to the dulcimer. So there's your little music lesson with mathematics for the day. So what we got here in the next group of guided practice problems, I call it the kitchen sink of alternating series. So I just wanted to pick one of these here and work with this one with you. In fact, I think I'm going to pick part C. Let's go on to part C. It says determine if the following series are absolutely conditionally convergent or divergent. So the very first thing that we need to do with this is focus on the summation, I should say, of the absolute value. I want to figure out what is going on with this guy, right? So if we think about the role that those absolute values play, well, certainly they just kind of wipe away the alternating term, the alternating component, I should say, 1 over the square root of n. I have something like that. And then we have to think about, okay, what do we have on our hands here? Well, we have a P series, right? P is obviously equivalent to 1/2. That 1/2 is less than 1, right? So we have a divergent situation. Now, what does that mean? Well, all it means is that we've lost any chance of being absolutely convergent. Right? We don't want to give up on the problem and say, oh, we're completely divergent all the way around, because that may not be the case. We've just lost absolute convergence. Right? Now what we have to do is go into the alternating series test. So we still use that concept from yesterday, which if you remember has 2 parts to it. That's why we reviewed it pretty heavily at the beginning of this video. And the first part is what is this limit doing of the non-alternating component, which is just the 1 over the square root of n. And as n grows really big, we can see that this is going to be 0, of course. And then we go into the second phase of the test, which is the nth plus 1 term of this non-alternating component less than or equal to the nth term? So I'm just going to simply replace the n with n plus 1 and question whether or not this is a true statement. And it's very likely just from that stage, you can probably use some slight intuition to gather that this is a true statement. Of course, if you do cross multiply, oops, I should have a square root of that. If you do cross multiply, you just have to make sure that the product that you put on the left side is the product that involves the numerator of the left side. And I would have something like this, I suppose, after we cross multiply. Let's say we want to continue this, we could square both sides, but with each passing step, subtracting the n from both sides, you're going to get to a place where you feel pretty confident, right? I think we can probably throw this in front of an elementary school age student to say, hey, is this a true statement, as long as they knew what this equality symbol meant. So we do check both of those particular criteria, which means the AST is saying that this thing still converges, but the summation of the absolute value said otherwise. That's the situation where we would say that this is going to converge conditionally, or you could say conditionally convergent. Okay, so there are 3 different things that obviously can happen in this situation. Okay, there are a lot of problems in this guided practice. Brian purposely wanted to write several of these so that you can get some extended practice with this, and they're all great. Each one just has a little bit of a different nuance to them. So I certainly would invite you to try some of these and certainly check them with the key that's now posted. Let's go ahead and take a look at a slightly different approach to this idea of absolute and conditional convergence. It's the same kind of concept, but it's going to have you sort of think at a slightly different level. So we got I call it the alternating series roundup. Yeehaw. So what I've got here is 6 different series, right, A through F, and we have a question that asks to find a value of k such that the summation -1 to the n of a sub n is conditionally convergent, but yet the summation -1 to n b sub n is absolutely convergent. And I'd like you guys to kind of think about this. I'm going to give you a minute or so, and about halfway through that minute, you'll hear some music play. If it's too loud, you can just kind of lower your volume, and then we'll see if we can check your answer. Take a look at this one. Wonderful. That music is compliments of Kareem, one of our listeners that submitted yesterday. Thank you for that. And if we take a look at our solution, find a value of k such that this particular series is conditionally convergent. Well, what we're going to do here is think about what a sub n is. Well, a sub n is our lead-off series over here, 1 over n to the k. So if you have to rewrite that, that's certainly acceptable. You can get definitely a better look on what this thing is really doing. And we notice that, okay, well, that's kind of our typical p series form, I suppose. And we learned that this alternating version of this p series will indeed converge conditionally as long as that k value does not exceed 1, right? We want this k value to be less than or equal to 1. Now, we also know that the k is going to be greater than 0 at the same time. So we'll kind of temper that a little bit. But we know that we have this k that has to be less than or equal to 1. But if we look over here on the other series, and I might go ahead and write him up to get a better look at what he's doing. And -1 to the n, there's the alternating component. And then what's b of n is defined as well. Brian has defined b of n to be this a n squared. So if you could picture squaring that particular expression, the 1 squared is not going to change. He's still a 1. And then n to the k squared allows us to multiply those 2 exponents to get 2 times k. And now we can get a little bit better handle about what's happening. Now, again, we want to make sure that this 2k, in order for this to absolutely converge, right? We want this to be absolutely convergent. We know that that has to be greater than 1. And we're talking strictly greater than 1, right? We don't want it to conditionally converge and let 2k equal 1. So if we solve this, we have k is greater than 1/2. Okay? Now, you'll notice that we sort of have a range here, right? We've got k being less than or equal to 1 on this side, and we have k being greater than 1/2 on this side. And what we want to do is put those 2 ideas together, and essentially we're going to find their intersection is what we want. So we have to think about all the values of k that satisfy this inequality and this inequality and this inequality. And so if you put those 2 ideas together, it's any k that's strictly greater than the half, right? Half is less than k, but at the same time, we cannot be any larger than 1. So we can be equal to 1 and of course less than 1. And that would be your range of k's there. But as you can see, if you have the document in front of you, there are 3 other versions of this that kind of filter in the other series and ask slightly different questions about finding the maximum value of k. It's an excellent problem. In part C, we're going to know that the first series is absolutely convergent. Determine if the second series that involves the f sub n is either absolute, conditionally convergent, or divergent. And then we have another part D here that wants to determine which alternating series has to be absolutely convergent given the condition here for the alternating C n series divergent. So there's a lot of great things going on with the problem. problem. It's a very well written problem by Brian. All right. So we have another phase here. Let's check for understanding that. Again, we wanted to throw a few more problems at you that dealt with the idea of the alternating series as an absolute convergence and conditional convergence, because it does take a while to practice these. I tend to give my students a few extra of these problems because it does have two different steps that you have to kind of isolate on. So again, we invite you to take a look at practice 2. We have, I think, 4 more there, A, B, C, D, and we really threw in a great one here, D. I'd like you certainly to give that one some attention because of the idea of the piecewise function approach. So if we summarize what we've been doing today, we find that our enduring understanding really hasn't changed. We're applying limits, and we know that applying them may allow us to determine, the finite sum of an infinitely any termed particular series. And the key takeaway here, well, the p-series. The p-series test is one of the very easiest things that we will probably learn in BC calculus, and we know that we will converge if that p-value is greater than 1 and diverge if it's between 0 and 1, inclusive of 1. And then we learned our alternating series test will allow us to extend it to figure out absolute convergence and conditional convergence by these 2 criteria that have been mentioned frequently throughout this particular video. So the common errors, misconceptions, or pitfalls, you want to always be careful to simplify your exponents when working with a p-series. It's probably likely that that's what you would encounter most of the time on a traditional AP exam. So do your algebra correctly as always. And then remember that alternating series can converge in 2 different ways. It's always best to start by determining the behavior of the series of the absolute value of that nth term expression first. And then once you determine if that's convergent or divergent, then you can go ahead and apply the alternating series test. All right. Your AP exam practice problem, your other homework assignment for tonight. Right? What else are you going to do? Right? Lots of good calculus practice that you can do between now and tomorrow. But we're going to define a sub n to be 1 over n to the k plus 1, where k is a constant. And in part A, let's let that k be a half, and let's have you use the alternating series test to show that that particular series does indeed converge. And then extend to determine if that series converges conditionally, absolutely, which of the 2. And then in part B, we're going to define a new nth term expression, b of n is a of square root of n. Let's find all the integer values of k so that this new alternating series converges only conditionally. And then in part C, appropriately, we're going to define another nth term expression, c of n, to be a of n to the negative 2k. In this problem, I want you to show that there is no real k value, so that this series is the harmonic series. So there's your AP exam practice for the night. And as always, we want to make sure that you, and not just you, but your friends, have wonderful access to the different resources that the College Board is providing. And of course, when it comes time to take the exam, we want to make sure that everybody has the same equitable experience so that they can have the most success possible. So please reach out cb.org/tech if your friends have any questions about how you can better obtain the various pieces of equipment, the various services that you can gain access to these wonderful resources. Our tweet out really quickly for our AP Teachers Rock, right? We're still doing that. Keep them coming. So as far as the AP Teachers Rocking, we are recognizing this particular teacher. Thanks for the quality live AP sessions. My AP calculus teacher is so knowledgeable and prepared, is willing to reach out and help all of our students, and is truly an amazing person and a teacher overall. I couldn't be more thankful. And I'll tell you what, that's a teacher I would certainly love to work with at my school. So thanks for that. And as far as AP Students Rocking, we actually have a good friend of ours. We're going to shout out to Brian, nice friend from Houston, Cedric French, who's an excellent advanced placement calc teacher down in the Lone Star State. And he says that he's very happy that students are working hard and preparing for the AP calculus exam. This is a tough time for everyone. It certainly is. And we're going to leave this quote. I think this quote says everything that we need to say. You guys are the true dreamers. Keep working, keep fighting. You guys can do this. We're going to get through this together. And that wraps it up. Tomorrow we got Brian coming in for a great session over the comparison tests, and that's going to lead into the end of the week for the geometric series. So without further ado, we're going to sign off now. We want you to have a great day. Please keep safe, keep healthy, and keep learning.
Calculus, Taylor Polynomials, infinite series, differential equation, calculus, Taylor Polynomials, infinite series, differential equation.
Well, good morning, everybody, and welcome again to today's edition of AP Calculus BC Live. Today we're going to be looking at topic 10.6, which is comparison test for convergence. I want to thank once again the very talented Kate Yevin for creating, producing, and sharing our intro music with the sultry voiceover by Chris Yevin. The other day, I asked you guys to send in some possible theme songs for Calculus BC because it doesn't seem important enough to have these daily each day unless we have a really cool theme song, and we have received several of those theme songs. And we're going to make sure that we try to work in as many as possible into our intros or exits during these lessons or even during the lessons. And so if you haven't had a chance to send one in yet, but you got that musical talent, I want to encourage you to do that and send them up to us, and we'll work as many as possible into these live lessons. So if you don't know, my name is Brian Passwater. I'm a high school teacher in Speedway, and every time we do these lessons, Tony and I will introduce ourselves, and it's starting to get a little bit boring, it seems like, because we're saying the same things over and over again. And so I thought I'd share a little bit more about myself this morning briefly. I was thinking, what can I tell you that you need to know that maybe you wouldn't know kind of automatically? And so the basic, I'm married with a couple kids. I thought I'd share a couple things that pretty much sum me up. And so what you're going to see here is a picture. I got a tattoo a couple years ago. I'm a pretty big math nerd. This is the tattoo of the zeta function, the Riemann hypothesis, which I became obsessed with when I was an undergraduate in college. I wanted to solve this poor problem, so I've been working on it for the last 13 years or so. A couple years ago, I decided to get a tattoo and make it official. My wife calls it my friend finder because if we're out public and somebody recognizes the tattoo, knows what it is, that's how I meet new friends. Something else you should probably know about me is I'm obsessed with the TV show The Office. I'm really sad once it leaves Netflix this year. I watch it pretty much every single day. I think I'm on my 25th or 26th consecutive viewing of the entire series. I watched it about 25 times straight through. I love going to do some Office trivia whenever I can find it. So before we get into the lesson today, I want to share a little bit of housekeeping items with you and remind you that every one of these lessons, the handouts and the problems that we do are available to you. You can print them off after the lesson, or you can print them off before the lesson, and you can follow along. I always include additional problems in each lesson that we're not going to get to. That way you can have some more practice with them. And so underneath each video, there's a hyperlink. If you click on that, it's the same link for every video. There'll be a Dropbox that's shared with you from Isaac Newton. You'll be able to find materials that we use each day. We also include in there after each lesson the detailed worked out solutions that our friend Ted Gott makes for us. That way you can check your work and also see if you're stuck on something, sort of some good path that you can take to solve those problems. Last week, I asked you guys to tweet out some positive things. If you're an AP teacher, I said, hey, tweet out what you appreciate and what you love about your students. And if you're an AP watching, I said, hey, can you please tweet out what makes your calculus teacher great or so special, or any AP teacher for that matter. And include the hashtag AP Teachers Rock or AP Students Rock. And each lesson, Tony and I are going to share out one or two of these with the whole group. That way we can share some of the positive things that are going out. And so today, our AP Teachers Rock tweet says a huge shout out to Ms. B, my amazing calc teacher. Not only does she encourage us to think outside the box and apply what we learned to the real world, but she has also been sending us hilarious math memes this past year. Hashtag AP Teachers Rock. All I know, Ms. B and students, I need to get my hands on some of these amazing, hilarious math memes. So I'm going to lay down a third challenge, right? I put the challenge out for tweets. You guys have been tweeting out daily. We appreciate that. I put the challenge out for intro music. You guys started off each morning and you guys have responded well to that. I need some math memes in my life. So if you got some great math memes, tweet them out. And if I see some great ones, I'll make sure that we include them at the end of each presentation. invitation to share out with the rest of the world, so we can all celebrate those memes. And then our AP Students Rock tweet says, cheers to all the AP students who are continuing their learning beyond the four walls of GRHS by consistently tuning in to the AP Live sessions. Thank you, College Board. Yes, thank you, College Board, for allowing Tony and I the opportunity to be here each morning with you. Tony and I talk right often about how humbled we are, how honored, how proud we are to be a part of this, to be a part of your learning each day. We are consistently amazed and impressed by how hard students are working right now when we're stuck at home during the days. And so we're very proud and we're very excited to be part of this. And we're grateful that you're joining us and that you're continuing to prepare for the AP exams that are coming up this spring. A couple of housekeeping items here again before we start our lesson. Upcoming lessons today is April 2nd. If you were here on Tuesday, you noticed the slide said April 1st on Tuesday. And I was genuinely caught off guard and surprised by the date. I wasn't really paying attention to what month or what day or anything it has been recently. And so I was like, wow, it's already April 1st. Well, dates were wrong. Tony played a little bit of trick on me because he made that slide for me, but I didn't really notice it. And then after my lesson, I received a whole bunch of emails and texts and tweets and messages telling me that I had the date wrong. And most people thought it was an April Fool's joke, early April Fool's joke. So I want to kind of play it off as if it was intentional, but really it was just me not even knowing what day of the week it is or what month we were in. But today is in fact April 2nd. And we're looking at comparison tests. And Tony's going to finish off our week tomorrow looking at geometric series. Next week, we're going to wrap up Unit 10, the last unit that's tested on this year's exam, by looking at a couple more tests, as well as jumping into some Taylor polynomials, approximations, air bounds. And then following next week, we're going to have 3 entire weeks, 15 consecutive lessons over amazing, incredible, life-changing AP Calculus BC exam prep and review. This is going to be the best review that you're going to get for this AP exam or your money back. Do not miss those lessons. They're going to be a don't miss, can't miss opportunity. We're Tony and I are going to do everything we can to make sure you are fully prepared for the exams coming up this spring. So at the end of each lesson, we give an AP practice problem for homework, and then the next day, that becomes our warm-up. So yesterday, Tony laid down this problem pretty well as the AP exam practice. So we're going to look at it today. I hope you get a chance to try it and maybe work it out a little bit. We're kind of putting a lot of things together from the last several lessons into one good conceptual problem. This is kind of the stuff that the AP exam is going to do typically to see if you really understand and can make connections between the different series of tests and ideas of learning so far. And so it's a really good practice to test your understanding and test your transferability of information. So this is the warm-up, and I'm going to go through the answers somewhat briefly. And I also want to share the answers this way today because one, because of time, and two, to share out with you, this is what the solution guides look like that we put up on Dropbox after the lesson. So this is the level of depth and detail that Ted gives us with the solution. So it's a really, really nice worked out solution that we can follow up. Part A says if K is 1/2, use the alternating series test to show that series converges. And then once we do that, determine that series will converge conditionally or absolutely. Well, Ted plugged in 1/2 here for K, and then we plugged in 1/2, the series became just -1 to the n times 1 over n to the 3/2. And so using the alternating series test, he had to do two things. Number one, show that the limit of 1 over n to the 3/2 approaches 0, which it did. And then two, we had to show that the terms are decreasing, or that a sub n plus 1 is always less than or equal to a sub n for some value of n on. And that was pretty intuitive. So both of those were true. And since both of those were true, those were our two conditions for the alternating series test. So then by the alternating series test, that series did converge. And then to figure out whether it converged conditionally or absolutely, then we then look at the series of the absolute value of terms. Well, when we do that, we get a p series that Tony talked about yesterday, where p was 3/2. And according to our p series test, since that number is greater than 1, the series converges. And since the absolute value of the terms converge, the series did, then that means the series converges absolutely. And then looking at part B, now we have this new function that b of n is now a of the square root of n. So we plug that radical in into the problem. We end up getting this series right here, where we get n to the 1/2 times the quantity k plus 1. And the question says, what would make this series converge conditionally? This is where we really get into some conceptual understanding, because this is sort of like a p series, right? It's an alternating version of a p series. So what would make it converge conditionally? Well, that would mean that it converges the alternating component, but it would not converge if it was gone, right? Conditional convergence means it only converged because the series was alternating. And so if we look at what the series would look like if it did not converge, or if it was not alternating, it becomes this p series right here. Well, what would make a p series not converge? Well, a p series will not converge, it'll diverge if the p value is greater than 0 or less than or equal to 1. So essentially, to check out when the series converges conditionally, we can just set our exponent 1/2 to the k times k plus 1 between 0 and 1. And then we can solve that inequality. And Ted kind of work this all out here really mathematically for us, but another way to think about this is just to solve this inequality by multiplying everything by 2 to get rid of the 1/2. And we get 0 is less than, k plus 1 is less than or equal to 2. And subtracting 1 from all three parts, we get that k is greater than -1 and less than or equal to 1. And the question wanted all integer values, okay? So the only integer values that would work would be 0 and 1, so we cannot include the -1 in our answer. And then finally, looking at part C, we have a third function. C of n is a of n to the -2k. And we want to show now that there's no real value of k, or that C of n is the harmonic series. Well, think about what the harmonic series is from yesterday. Harmonic series is just a p series. Remember, where p is equal to 1, so it's just 1 over n. And we want to show there is no k value where that would be harmonic. Well, this is what the series looks like right here. And if it were harmonic, that means the exponent would have to be 1. So when it says show there's no real value, whenever an AP prep question says show something, really what that means is treat it as if it said find, right? It says show there's no value. It's kind of asking you to say find what k would be. So you would solve for it. And whatever you get, you have now shown whatever answer they wanted. And so Ted just set this exponent equal to 1, so that's what would make it harmonic. And then we start to solve this quadratic equation. It becomes 2k squared plus 2k plus 1 is equal to 0. It doesn't factor, but we can use a quadratic formula. And we do the quadratic formula, look what happens. Inside of the radical, we get this -4. And we know that the square root of a negative number is going to be an imaginary number or a complex number. And so in this case, the only way to solve for k is to get an imaginary answer, which is not a real number. So we've now shown that there's no real numbers of k that would make that work. So thank you, Ted, for creating such great detailed worked out solutions. You're going to see solutions like this as well as solutions to all the problems there in the Dropbox following our lessons. So today, let's talk about what we're going to be learning about. I mentioned it already. We're going to be using the direct comparison test to learn about convergence and divergence, as well as the limit comparison test for convergence and divergence. And then throughout the lesson, we're going to be hopefully tying all these previous tests together so you can see how they all fit in and intertwine in different types of problems, right? And so remember, the tests that we've talked about so far, so we're going to limit ourselves to just the tests that we've done here. We know there's more tests that some of you have seen if your class has gone further in the curriculum already, but we're going to limit ourselves to just certain tests to see if we can use these tests. And we talked about the nth term test for divergence. We talked about the p series, right, test. We'll be talking about the direct comparison test today, as well as the limit comparison. We did the alternating series test the other day, as well as the idea of absolute versus conditional convergence. And so we're going to do all the problems with that. We're not going to be using the geometric series, which we'll do on Friday this week with Tony, and we're not going to do any of the ratio test because that will be next week, right? What should you know already that to make yourself successful? Well, hopefully, if you've been following along, you've gotten lots of practice at evaluating limits at infinity. We remember our p series rules for convergence from yesterday, and then our nth term test for divergence from last week. And by the end of the lesson, we'll not just know how to do basic mechanical problems of direct and limit comparison, but we'll have a depth of understanding that will allow us to tackle more of these abstract problems that are making a lot of connections. Like if 0 is less than a is less than or equal to b for all n, and the series of a sub n diverges, then what do we know about the limit of b sub n? So in order to answer a question like this, we're going to have to understand a couple of things. Number one, how does the direct comparison test work, and what does it tell us? And then second of all, how can I apply that and use the nth term test or the idea of convergence in general to make a decision about b sub n if we can at all? So the guided practice is what we would call like the notes part of our lesson. And so here's the notes for today. And before we actually dive into what the direct comparison test is, let's play a little game of logic, shall we? It'll be a pretty easy game, I promise. And I want us to think about two different situations. So situation number one, when my children were younger, this is a true story, by the way. Adapted a little bit, but this basically happened to us. When my children were younger, we went to a local carnival and we wrote down those big slides, right? You know what I'm talking about, those really big slides where it's like you have those burlap sacks and you write down like the big yellow slide, has a little bump in the middle. So we all wrote down those big slides as a family, we had a little bit of a race. And once we were done, my son wanted to go on it again, but he wanted to go alone this time. He was pretty young at the time, maybe 4 or 5 years old. He wanted to go again, he wanted to go alone. Well, unfortunately, when he went back to the line, guess what? He was not tall enough. I remember these little signs that you just tall to ride these rides alone. So here's my son. He was kind of like this. He was pretty sad because he wasn't quite tall enough. And if you watched us yesterday, you got to see Tony bring out his guitar and kind of show his talent on the guitar. I felt a little bit left out that Tony got to share his talents. So I thought today would be a good day to share my talent of drawing, because this is pretty much a spot on picture of my son. If you see him, you recognize him right away. He's a little blue guy, skinny, that has a little frowny face on. So he was not quite tall enough to ride the ride alone. Well, my daughter's a couple years older than he is, so she's taller than he was at the time. She wanted to ride the ride alone. Well, if she's taller than him, do you think that she is tall enough to ride? Take a quick second to think about that. My son wasn't tall enough. I drew a little picture of him. My daughter is taller than he is. Is she going to be tall enough to ride? Well, hopefully you're realizing we really don't know yet, do we? Right? Because he wasn't tall enough, and she's taller than him. So maybe she is this tall, or she's taller than he is, but she's still not quite tall enough to ride. Or maybe she's a lot taller than he is, and she did barely reach the height that we need. We don't really know. We don't have enough information to compare the heights to determine whether she was tall enough to ride or not. Well, later on that same day, situation number 2, we decided to play some carnival games. And both my kids played way too many games, like we always did, and they came away with a whole bunch of tickets to redeem for some prizes at the end. And my son's always the lucky one, so he won a jackpot on one of those games. So we had a whole bunch of tickets, right? So we ended up getting more tickets than my daughter did. And there was this really big prize that he won. I can't remember what it is now, but you know how they always have those big prizes on the shelf where it's like 10 million tickets to win. No one ever has any chance of winning it. You look down your pocket, like 48 tickets. You're like, oh man, 9 million, I could have that. So my son wanted this prize, but he was like 5. He doesn't understand the idea of how numbers work that well. But he didn't have enough money to win the tickets. Well, my daughter also wanted the same prize, right? So she wanted the same prize, but she had less tickets than he did. So do you think that she had enough tickets to get the prize? Well, obviously, if less than he did, then certainly no, she wouldn't, right? Now, the logical thing would have been, hey, why don't you guys pool up your tickets, put them together, and have double the tickets, and then go in together and get something bigger. But due to the sibling rivalry they always had, that never would have worked, right? So they all wanted to buy their own stuff, and neither one of them had enough tickets to buy whatever that big prize was individually. So both of those situations are going to set us up for what we're going to be doing today, which is the direct comparison test. And they're going to show you how it works, and also some things where it doesn't quite work the way you want to, right? So going back to our lesson from yesterday about p-series, look about the series 1 over n squared, right? And we know from yesterday that that's a p-series, and because the p-value is 2, and 2 is greater than 1, that series converges, right? P-series says the p-value is greater than 1, then the series will diverge, or converge, I apologize. But what about these two series? What about the series 1 over n squared plus 1? Or what about the series 1 over n squared minus 1? Well, those aren't technically p-series, right? A p-series is just 1 over n to the p. It doesn't count or doesn't allow for us to have anything else being added or subtracted. It's just 1 over n to the p power. It doesn't allow us to have this plus 1 or this minus 1. So we can't apply the p-series directly to this. Now, hopefully, intuition, our gut instincts will tell us or give us a hint about what this is doing, right? I mean, what do you think? If 1 over n squared converges, what do you think is going to be happening with, intuitively at least, 1 over n squared plus 1 or 1 over n squared minus 1? Well, hopefully we understand that that little plus 1 or that little minus 1 in this case isn't going to really do enough to impact whether or not the series converges or diverges, right? So if 1 over n squared converges, it would make sense that 1 over n squared plus 1 would also converge, or 1 over n squared minus 1 would also converge, because that shouldn't change the outcome of the problem. Now, certainly, if it converges, it'll be a different answer. It'll converge to a different number, but it's still hopefully going to converge. Well, how do we take that intuition or that kind of gut feeling and apply it more mathematically? And that's where the direct comparison test is going to come in. And later on today, the limit comparison test will come in as well. So here's what the direct comparison test says. If a is greater than 0 and b sub n is greater than or equal to a sub n for all values, then if the series of b sub n converges, then so does the series for a sub n. And if the series a sub n diverges, then so does the series for b sub n. It seems like a pretty simple idea on the surface, and it really is, except sometimes we get these little nuanced problems. We have to be careful what we know and what we can apply, because just like the nth term test, students will often misapply or misuse or misunderstand what this test actually says, right? These are if-then statements. If you remember much from your class, this is a conditional statement, and we have a conditional statement. We don't get to assume that the converse or the inverse are true statements as well. So sometimes students will use the converse or assume the converse is true or assume the inverse is true, and usually it's not. And I'll explain what I mean by that here through a couple of examples. So I'm going to take a step back for a second. We're going to look at the direct comparison test again, and we're going to see what it says, but also we're going to see what it does not say, right? And so I'm going to preface this. I'm going to put down here on the bottom of the page for a second to all of the teachers that are out there. Please do not send me any hate mail over this, please. And here's what I mean by that is I'm going to step back. I'm going to be a little bit unmathematical for a second, okay? A lot of times with series in particular, as math teachers, always trying to be very precise, very technical, and very correct. But we do that, it involves a lot of symbols, a lot of notation, a lot of vocabulary, a lot of mathematical jargon, and we do all those things. Sometimes we take some basic simple ideas and we complicate them unnecessarily and end up confusing people. So what I'm going to do is take a step back from all this technical mathematical precision for a minute and just get to the heart of what this really says. So we're going to look at this from a more kind of non-mathematical, logical way to make sure we really understand what this test is saying and what it's not saying. And then we're going to come back to the mathematical side and prove all these things or do all these things properly, right? So I'm naming some things. Yes, I know this is not mathematical, but I think it's going to give you a better idea of what's happening. So please don't send me hate mail until after you see the whole lesson, in which case, if you still don't like it, feel free to do that. So here's how I think about the direct comparison test. I always imagine all series as either living in this land of divergence, right? Up here is sort of this land of divergence. So up here's where all the series diverge would live, and then down here is the land of convergence. So all the series that converge live down here, and then there's this magical sort of dotted line separator that divides all of the divergent series from all of the convergent series. And every time we learn a test, when we learn the nth test, when we learn the p-series test, when we learn the alternating series test, today we learn direct comparison or limit comparison or the ratio test next week or geometric series tomorrow. Every time we learn a different test, really what we're doing is we're trying to figure out where that dotted line is. We're trying to figure out where's that separation between what makes a series diverge and what makes a series converge. And depending on what type of series we have, depending on how that series looks, how we find that dotted line, how we find that separation. So we learned when we had p-series, that dotted line was based off of the value of p, right? And so if the p-value was not more than 1, the series would diverge. So up here in this world of divergent series would be things like the harmonic series of 1 over n. But down here in the land of convergence, we would have series like 1 over n squared, right? We might have some series up here in the land of divergence, just something like -1 to the n power. That would diverge by the nth term test because the terms don't approach 0, right? Or we might have down here in the land of convergence, maybe the alternating harmonic series, -1 to the n over n. So we have these a whole bunch of divergent series up here, a whole bunch of convergent series down here. So let's think about these statements that the direct comparison test is making. Let's also think about what it's not saying, which will be really important here in a few minutes. So we're going to call the series a sub n capital A to make it easier. So we're going to call the series b sub n capital B to make my work a little bit easier. And remember, this is a key part here, right? That a sub n is less than or equal to b sub n, which means that the series A is less than or equal to the series B. And so if the series B converges, that means that capital B is somewhere down here, right? It's somewhere down here in this world, this land of convergence, it's a convergent series. So what can that tell me about the series A? Well, since A is less than or equal to B, then A has to be either below or equal to B, which means I can only go down in this direction. If I go down from wherever series B is to a lower value, then certainly series A is still going to be down here in this land of convergence, right? So B converges, so does A, no problem. But what about the second part? What if A diverges, right? So now we know that capital A is going to be somewhere up here in this situation, in this land of divergence. What do we know about series B? Well, B is bigger than A, so if B is bigger than A, we're going to have to go up, right? If we're higher, it's a higher value. Well, A diverges and B is always bigger than A, then B has to be up here somewhere. Well, if I'm going up, I'm already in this land of divergence. Certainly B is also going to have to be in that land of divergence. So those two ideas are pretty straightforward. But here's where I think it gets a little bit tricky. Here's where that first situation I talked about with my son and my daughter writing that slide side comes into play. Because what if series A converges, right? What if we know series A is down here somewhere? So what if series A converges? Remember, we know that series B is above series A, but A is down here in this convergent area, and I'm going up because B is higher. How can we figure out whether B is still going to be in that area of convergence? It could be, right? I could go up and still be in the land of convergence. Or how do we know whether or not we go up so far that it passes over this line into the land of divergence? We really can't tell. And then conversely, what if series B diverged, right? What if series B diverged and we know that A is less than B, so A is going to be lower? Well, again, how do we know how far lower it is? How do we know if it's low enough but it's still going to be in this divergent area, or whether somehow it's low enough that it crossed over into this land of convergence? Again, we don't know. So when we're doing the direct comparison test, we have to be really careful about what series we're using to compare with and what really we can say about it, right? So I like to kind of draw these pictures, especially with more of the abstract conceptual problems. We don't actually have a real series to work with, because it helps me understand what I can and cannot say about the different series. So let's see this in action, right? So we start off this idea with this series right here of 1 over n squared plus 1, and we're going to use the direct comparison test to sort of hopefully reinforce or solidify what we thought intuitively that this should converge, right? And so our natural idea is we've got to compare it. Whenever you do a comparison test, you have to compare it to a test or a series that you know what it does, right? So the most natural comparison is going to be 1 over n squared, because I know that 1 over n squared converges. How do I know it converges? Because the p series, where p equals 2. And yesterday we learned that a p series, when the p value is more than 1, will converge. And then this series right here, remember it says, look, if the series that you're comparing it to, if this series is less than this series, then that means it's going to follow the same convergence rules, right? So essentially, here's what we have. I kind of draw this dotted line again. I know that this series, 1 over n squared, is down here somewhere in this convergent. And then now I compare the terms. Well, look at the terms, 1 over n squared plus 1 compared to 1 over n squared. Well, since I'm adding 1 to this denominator, that means that this denominator is always going to be a little bit bigger than this denominator, right? So it's going to be 1 more than this one. Well, this denominator is bigger than this denominator. That means that this fraction is going to be less than that fraction. And so since these terms are always less than these terms, that means that this series is going to be less than this series, right? Well, if it's less than this series, then I know that's going to be going downward somewhere, and it's still going to be in this area of convergence, right? So by the direct comparison test, since 1 over n squared plus 1 is always less than 1 over n squared whenever n is at least 1, then the direct comparison test tells us that because of this, 1 over n squared plus 1 from 1 to infinity converges. And we're going to say by the direct comparison test. And whenever we're doing a comparison test, it's really helpful to tell what we compared it to. We compared it to 1 over n squared. So that's a really nice example of how the direct comparison test would work for convergence. What about how might it work for divergence? Well, example 2 is 1 over the square root of n minus 3, and the natural test to compare it to would be the series, hopefully, 1 over radical n. 1 over radical n, don't forget, is the same thing as 1 over n to the 1/2 power. This is also a p series, right, where p is equal to 1/2. Well, because p is equal to 1/2, that's less than 1, so that means that this series diverges, right? It's a divergent series. And so that means, if I were to draw my little picture here, that the 1 over radical n series is going to be up here somewhere, right? Well, hopefully, the only way I'm going to make any kind of determination about this series is if I can somehow show that these terms are bigger than these terms, right? Because if this is up here, if these terms are all bigger than 1 over radical n, then I know that it's going to be higher, which means it would still diverge. Well, let's see if we can show that. 1 over radical n minus 3. If we compare that to 1 over radical n, notice we're starting here at n equals 10. Well, we start at n equals 10 because if we started at anywhere below 10, like 9, for example, square root of 9 minus 3 would have given us 0 in the denominator, which would have been an undefined value. And so we're just going to be safe and start at 10. Well, this fraction right here, since we're subtracting 3 from these denominators, that means this denominator is always going to be a little bit less than this one. And this denominator is less than this denominator. That means that this fraction is going to have to be greater than that fraction, which means my series, since these terms are all greater as long as n is at least 10, it means that this series is going to be bigger than this series, which means it's going to be up here still, which means we're going to be divergent, right? And so that means that the series diverges, and then we're going to say by the direct comparison test, and then to the series 1 over square root of n. Now, there's a couple of examples of how we can use the direct comparison test. We're not going to look at example 3, but it's there in case you want to try it. And I would encourage you, if you try this, to see if you can solve it without using any geometric series, right? Because we haven't done geometric series yet, so I purposely threw something that has some geometric series in it to see if we can solve it using some partial sums ideas from the other day. Now, example 4 is a little bit more of an abstract question, so we're going to really get to the heart of it if you understand what these things mean, how we can apply it, especially if we don't have a given explicit function or a given series to work with. And so the same rules apply if 0 is less than a is less than b, and if the series a sub n diverges, which of the following must be true? That's the key here, must be true. So here's what we know. We know that the series of a sub n is somewhere up here, right, in this divergent world. So if a is up here, what do we know? Well, this is a really neat question, because take a second and look at your a, b, c, and d. I'm going to give you a few seconds. I'm not going to put a timer on here, but I'm going to give you a few seconds and see if you can think about which ones you think must be true. To make it a little bit more interesting, I'm going to tell you it's possible that none of them must be true, or one of them might have to be true, or more than one. So I'm not going to say whether there's one answer, more than one answer, or no answers. But take a few seconds, take a look at these, and see if you can figure out how many or which ones, if any, must be true. So I'm going to start with the one that might be the most obvious compared to what we've just been talking about. Since we know that b is greater than a, then to get to b, I have to go up, right? So the series for b sub n is going to have to be greater than a, is going to be up here somewhere. So what do I know? Well, a diverges, then b has to also diverge, right? So we know for certain that d must be true. But what about the other ones, right? We know that the series for a diverges. What about this? See, this is just the alternating version. We did learn that it's possible that a series might diverge, but yet if it alternated, it would converge, right? That was the idea behind Tony's lesson yesterday, talking about conditional convergence, right? Well, it is certainly possible that this alternating version could converge. Unfortunately, we don't know if it has to, correct? So this doesn't have to converge. It could, but it's not true. I mean, in terms of it has to be true. So we can cross C off. Then what about a and b? These are kind of the same ideas. The limit of a sub n does not equal 0, and the limit of b sub n does not equal 0. Well, we know that a and b both diverge, but does that mean that their limits don't equal 0 of the terms? And the answer to that is no, right? Because the in-term test from the other day says if the limit as n approaches infinity of a sequence does not approach 0, if the terms don't approach 0, then, right, arrow number then there, the series diverges. That's what the in-term test says. We don't get to make any other assumptions about that. Meaning here, we know that the series diverges. We don't get to go backwards and assume that this is true, right? That would be called the converse of this conditional statement. And just because you have an if-then statement doesn't mean you can turn it around and still assume that it's true, right? A really simple example of this would be, I live in Indianapolis, right? So if someone lives in Indianapolis, then they live in Indiana. That's a true conditional statement. If you live in Indianapolis, then you live in Indiana. Well, if I turn that around with the converse and say, if someone lives in Indiana, then they must live in Indianapolis, which is clearly not a true statement, right? And so we don't get the current statements around. If something diverges, it's very possible the limit of its terms could approach 0, right? For example, what if a sub n was just 1 over n? What if that series was just a harmonic series? That certainly diverges, doesn't it? The terms still approach 0. So a is out and b is out in terms of they don't have to be true. It's possible they might not equal 0, but they're not here. So the only correct answer was D. You're going to see a lot more of these abstract conceptual problems on the file in that Dropbox folder. So it's really good practice to jump in and try some of these, because it really will test the nuances of how well you actually know these different tests and these different theorems. So I'm going to show you a quick example of why we need a limit comparison test, because the other series I gave you was this 1 over n squared minus 1 series. But in this case, it would be more natural. What series we compare it to? Well, my first instinct would be to compare it to 1 over n squared, right? That would be the natural choice. Well, think about where 1 over n squared is. Well, that is certainly going to converge, right? Because this is a p series or ps2. But then if I'm comparing it to this series right here, 1 over n squared minus 1 is actually going to be less than 1 over n squared whenever n is greater than or equal to 2. Because if I'm subtracting 1 from this denominator, it's going to make this fraction bigger than this one. Oops, I had that backwards, didn't I? I caught myself this time. 1 over n squared minus 1 is bigger than 1 over n squared because if the denominator is a little bit smaller, it's going to make the overall fraction a little bit bigger, isn't it? So if 1 over n squared is down here and 1 over n squared minus 1 is bigger than that, that means that that series is going to be a little bit bigger. But that gets into that problem we had, like my son and my daughter and their heights, right? So if I'm going a little bit higher, how do I know how much bigger it is? Is it big enough to cross over that sort of imaginary line to this world of divergence, or is it not enough to cross over? Well, our intuition might tell us, well, clearly it's going to still verge, but we can't use the direct comparison test with 1 over n squared to do that because it's not going to give us the right comparison that we need. Now, there are some ways that we could do this. We could come up with a test, right? We can compare it to something like 1 over n to the 3 halves. We could do some stuff like that, but it starts to get a little bit trickier to guarantee that the terms are always less than something else. And so it leads us into this other test, a little bit more powerful test, a little bit more robust, called the limit comparison test. And all the limit comparison test says is if a is positive and b is positive, then if you took the limit of the ratio from a over b, if that equals L, where L is a finite, meaning a real number and positive, then both of those series will either both converge or both diverge. So what we're doing is we're trying to find a comparable series like we were doing with the direct comparison test, and then all we have to do is take the limit of their ratios, and if that limit equals a positive real number, right? Got to be positive, it's got to be a real number, then we know that those two series behave the same. Meaning if one of them converges, the other one does. If one of them diverges, the other one does. They're going to live sort of the same world. So let's see how we can apply that to that 1 over n squared minus 1 problem. It's going to make the most sense, again, to compare this to 1 over n squared. Well, what do we know about 1 over n squared? Well, certainly this series will converge, right? Because the p-value is 2. But using the limit comparison test, we're taking the as n goes to infinity of 1 over n squared minus 1 divided by 1 over n squared. We're going to divide the ratio of those two sequences. Now we're going to do a little bit of manipulation here with our fractions. We're dividing by fractions. So really we're taking 1 over n squared minus 1 times n squared over 1. And then that becomes, if I go ahead and multiply that, we're going to get n squared on top over n squared minus 1 on bottom. Well, the limit as n goes to infinity of n squared over n squared minus 1 is just going to be 1, right? It's the ratio of those coefficients. And the limit comparison test says if that limit equals a positive real value, hey, 1 is a positive real value, then the series that we want to know and the series that we are comparing it to will have the same outcome. And so since 1 over n squared converges, then 1 over n squared minus 1 is also going to converge. So we can say that this series converges by the limit comparison test to 1 over n squared. So that's a really good example of why we use the limit comparison test. The limit comparison test, really what it does is it confirms all those intuitions that we might think should work. So the really key about limit comparison test is to know which series to compare it to. And the easiest way to do that is ignoring everything except for the largest exponent in the numerator and the largest exponent in the denominator. You look at just those and reduce that ratio. That's the series that you should compare it to. So for example, in this case, I would compare this series to n squared, that's the largest power on top, over n cubed. And then if we reduce that, we can compare this to simply 1 over n. So I was going to do the limit comparison test. I would do the limit of 1 over n compared to this series right here. And we know when we do the comparison test, if you choose the right series to compare it to, they're going to have the same outcomes. And so since 1 over n is a harmonic series, a p series or p1, since this diverges, I know that the original series is also going to end up divergent. And we can set that ratio and solve that as well. Something like this one, right? It has some radicals in it, but it's not going to be too tricky. The square root of n plus 1, well, the largest thing on the top is just going to be that radical n. And the largest power, the most dominant power on the bottom is this n to the 4th. So if I try to reduce this series, n to the 1/2 on top and n to the 4th on the bottom is going to end up being n to the 7/2 if I subtract those powers. Well, to the p series where p is greater than 1 in this case. So I know that both of these series are going to end up converging once I do my limit comparison test. I'll leave this last one for you to try at home as we get ready to wrap up here today. It's a nice little problem. I always like to give some regular problems where you're kind of manipulating, right? It kind of goes from easy to medium to more challenging questions. A basic question, a little bit more interesting ones, some radicals involved, and then something a little bit more non-specific, right? Where I have a k involved, you have to sort of have some ambiguity there. If you can do problems like that, then you know you really understand what these concepts are. So I'm going to leave that one for you so you can try that. And so there's a couple different problems here that we can try, and again, there's a whole bunch of them there you're welcome to try, and Ted has all these worked out solutions for you, which is really good practice. And then I want to point out something that's the check for understanding. There's an activity that we'll put in the Dropbox that's called which does not belong. And really each question has 4 different series, and then there's different answers that could be correct, right? So no, like this is the right answer, but just getting you into the habit of recognizing series, right? We did integration, think back to integration. The integration, the most challenging part to integrate was recognizing what strategy to use, recognizing what type of integral to use. Is it going to be an inverse tangent type problem? Is it going to be a U substitution problem? Is it going to be a problem that's going to end up being a natural log when I'm done? Am I going to have to use integration by parts? Am I going to have to use partial fractions, right? The hardest part of integration is identifying what type of question it was, and once you knew what it was, then you sort of have some procedures to go about and to do it. Well, series are very similar to that, where the most challenging part is recognizing on the front what kind of problem it is and what strategy you should use. And so this is a really good activity to get you into that habit, just practicing that skill of recognizing different types of series so we can get a better sense of how to categorize them and how to start these problems. And so there'll be 4 problems, and you're going to identify which one is different from the rest. And there's different reasons. Sometimes it's because one of them diverges and the rest of them don't. Sometimes it's because one of them is, or all of them are geometric except for one, or all of them are p series except for one, or all of them fail the interim test except for one. So there could be some multiple different answers, but you can play around with it. We'll have that file in the Dropbox for you as well as a couple of other of these check for understandings. And then I wanted to point out, don't overlook this last practice 3 problem because it really gets to the heart of your depth of understanding. Here's an intro, right? If something is true, so question A, if the series B diverges, there's 4 things here. This is not a multiple choice question, right? As I input A, B, C, or D for choices, for each one of these, you're going to decide if these conclusions are always, sometimes, or never true. They're a little bit trickier than you think, and they're really going to make you think about these ideas because we don't have an actual given explicit series to work with. You're going to have to think about how all these things connect. So try those out, compare your answers with the answer keys that you see. So let's talk about what we did today. We talked about the direct comparison test, and we talked about the limit comparison test. Hopefully they start to make a little bit more sense to you today. A couple of things that we see students do incorrectly on this is sometimes they will misapply. And when I say misapply, that's what I was talking about with that first situation where you compared it to a series, but however, the connection between the 2 series doesn't allow us to make a valid conclusion, right? So we got to be careful that we're picking the correct series and that we're making the correct conclusion if we can even make a conclusion. And then with the limit comparison test, it's important that the value L that we get, this is not the actual sum of the series. Sometimes students think because it becomes a number, you do the limit comparison, you get 2, or you get 4, or 1, or something, and think, oh, that must be the actual answer to the series. Remember, we don't actually know what the answer to these series are. All we're deciding is, do they converge or do they diverge? We don't actually say what they converge to until tomorrow when Tony introduces us to the geometric series test. And then also don't forget the value L needs to be a positive value. If it equals 0, then that test failed, and most likely we compared it to the wrong series. If you don't get a positive real number, then you probably compared it to the wrong series. You made a mistake in how you should simplify or reduce that. So your AP practice for the day, I'm going to leave you with this. Another nice conceptual problem in the beginning. I'm going to give you 3 different sequences, A sub n, B sub n, and C sub n. Notice case grade 1. This is a 4-parter. Wow, I'm really setting Tony up for some challenges tomorrow. I'm learning as I write these AP exam practice problems that when I get a lesson, I can make the problems really, really hard because then Tony has to deal with the aftermath. He has to walk you through them. If you saw yesterday's AP practice problem, or yesterday's warm-up, then Tony did a masterful job explaining it because I really laid the gauntlet down and thought I would come up. He came through. But I also realized when I have his AP practice problems on his lessons, I'm going to be doing those during my warm-up. So I'm going to start making his practice problems that he gives you a little bit easier. That way it makes my life easier. And I'll make the challenging ones for him to deal with. We have 4 parts there, and this is again in that file in the Dropbox. But if you don't have access to a printer, you don't have a chance to get the Dropbox, take a quick picture of this and see if you can't try some of these. I'm going to encourage you to really try these because these 4 problems connect all these ideas we've been talking about, all these series tests and all these connections. You're going to have a chance to work with them all together in one problem and really give you a good feel for whether you're ready or not for the AP style questions that you might see. Wonderful. So as always, we want to remind you that the College Board's well aware that sometimes there are some issues with getting connected or getting mobile tools or connectivity to either access the AP Classroom or the AP exams that are coming up. If you or anybody else that you know might have a concern or issue with that connectivity, please reach the College Board directly at the website cb.org/tech, and they'll make sure they work with you to get you what you need to be fully prepared and ready to take the AP exams. And I'll leave you this quote: "You miss 100% of the shots you don't take." Wayne Gretzky by Michael Scott. If you're a fan of The Office, you will understand that reference. Even though it's a little bit silly, it's true. If you don't take the shot, there's no way that you can make it. And so thank you all for being here, for taking your shot, preparing for the AP exam, and to give yourself the best chance to be fully prepared for what's going to be happening this spring. Thank you for joining us. Thank you for watching. Don't forget to join in tomorrow for Tony's lesson over Geometric Series. It's going to be a great one. Have a great day, you guys.
Calculus. Polynomials. Infinite series. Differential equation. Calculus. Polynomials. Infinite series.
Good morning, everyone, and once again, thanks, Kate Yetman and her father, calculus teacher Chris Yetman, for the wonderful rendition of our theme song that we're going to use here over the next few weeks, probably. The song's starting to grow on me. Brian and I had a conversation about that. So again, thanks to the both of you. Welcome to our second Friday here with our AP Live, AP Calculus BC edition. We're going to be talking about, obviously, working with geometric series today, which is another pretty simple test that will probably allow us to solve some problems that don't take a whole lot of time and effort, just a few steps to kind of get the conditions of this test squared away and whatnot. We have, once again, several documents that you all have access to. So as always, you can find the link to our Dropbox file in the description to the video. And you still have a little bit of time if you want to print that out really quick and use that as we go through some housekeeping items. But I am Mr. Tony Record. I'm a calculus teacher at Avon High School, one of the calculus teachers. I'd like to give a shout out to my colleague, Mr. Kyle Minier, who's been working alongside me for the last 3 years. He does an excellent job with our AP students. So Kyle, thanks for all your help. You'll notice my background is a little different. I live in a state, like maybe some of you live in, where our governor just declared yesterday that we will not be going back to school for the 2019-2020 school year. And it is a little disappointing. You got, it's very likely that you have a lot of passionate teachers in your life, and I know that for the teachers that live in those states, that's pretty tough. We're now the 11th state to make that decision, and it's likely that we may not be the last state. And so if you are in that situation, we definitely feel where you eventually find yourself in that situation. And I speak for Brian. I know that when we say that, our heart really goes out to those of you who are 12 graders, because we know that this is a little bit rougher on you. But trust in the system, trust in your school corporation, trust in your leaders, because there's a lot of creative people, and I think we can put our heads together and try to create some very creative solutions to things like graduation and certain ceremonies and so forth. So all is not lost. All is not lost. And you're going to understand that probably a little bit more thoroughly when we get to the end of the lesson today, because we're going to talk to you about a story about how people can rise in the face of adversity. So this is my classroom, right? I'm actually in my living room, but it's my virtual classroom that I'm going to use today. And this is where I teach every day at Avon High School. It's just that I won't be back there teaching students for probably a few months, but we're okay with that. All right. So our agenda for the day and the week ahead, as I said today, we're going to talk about geometric series today. It is a starred content, so that means that it is slated to appear on the 2020 AP exam. And then moving ahead to next week, Brian's going to lead us off with radius and interval convergence. So maybe I give the power series to you, and then we'll kind of progress to our last convergence test that you'll need to know, the ratio test, and then talk all about Taylor approximations and then error bound at the end of the week. And then boy, we start really hitting the ground and running with our AP Calculus BC exam review practice going to take place beginning April 13th and running for 3 weeks. Now, because I'm a little melancholy about school being closed, we have some bonus content today, right? So you are going to be among some of the first people in the country, first students, I should say, to learn a little bit more about your AP Calculus exam. The information was shared with all advanced placement teachers last night, and the official proclamation, the official documentation is going to be available later this afternoon, but we have been given permission to talk to you a little bit about that. So I'm going to lead off with that here in a moment. And then at the end of the broadcast today, we're going to take a field trip. I forgot to tell you about that. Did you guys get your permission slips? Everybody got their permission slips? You in the front row teachers? All right, thanks. Yeah. All right. So we're all set. We got our permission slips. So we're going to take a quick field trip at the end of the day to Grantham, England. So what are we talking about this year's AP Calculus BC exam? If you want to take a photo of this, I suppose you could. This information is going to be out. I'm not going to spend a lot of time talking about it because Brian and I are going to go over these in a lot more detail when the time comes. But your Calculus BC exam is set to be administered Tuesday, May 12th. So that's a week later than it normally would have been. And it would be at 2 o'clock Eastern time. There is a makeup date. That would be Monday, June 1st. You're highly encouraged to go ahead and take the first one. We'll talk later about how you know you're taking the first one, what kind of protocol that you would need to follow. We'll take care of that later on. But we highly encourage you to be ready to take that one on May 12th in case there's some technical glitch issue, internet goes out, power goes out, so that you have that backup date for June 1st. The two tests would be obviously a little different. The questions would be different, of course. The test will consist of 2 free response problems. I think you have already been aware of that. The first one is set to carry a weight of 60%, and you would have 25 minutes to sort of download that problem, read through it, solve it, and then there's a 5-minute upload time that you would have to get your solutions, sent back to College Board so that you can open up the second question. And you would not be able to go back to the first question once you finish it. And the second question would be 40% of your grade. You would have 15 minutes to solve it within a 5-minute upload time. Now, what do we mean by upload time? Well, students can take this exam either by entering solutions via a keyboard, right, on your computer, or if you have a mobile device, you can use a touch screen, I suppose. The other option is you could actually do your work on a separate sheet of paper, just the old-fashioned way, pencil and paper, and you could take a photograph of that with your phone or other kind of device. But at that point, you would have to send that particular image to your computer so that you could then upload it, right? Or I suppose if you're actually taking the test on that mobile device, you could just attach that picture to the interface that's there to have that uploaded. So a lot of this is kind of in the preliminary stages, and like I said, Brian and I will talk a lot more about this, but it just gives you an idea. You can start thinking about what strategy you want. What device are you going to use? Start thinking about that right now. Are you the type that will be comfortable with keyboard input, or would you rather do the pencil and paper and attach the photograph input? If you are a keyboard input type person, I know you might be thinking keyboard input, that's not going to work. It seems like it would be very easy to do for AP Lang or AP Lit or what have you. But in calculus, you got your symbols and so forth, just like you would say in a physics course. Well, the College Board is going to issue sort of a keyboard input tip sheet weeks before the exam. So you'll have that to kind of look at. I'm sure that's something that Brian and I will go over very thoroughly too. So here's your preliminary information. A lot more details are going to be coming later, but at least you know the date, and at least you know a little bit about the protocol. Right? So hopefully that helps you a little bit. All right, our warm-up. It's another doozy. Thank you for that, Mr. Passwater. We had a wonderful question here. And I tell you what I like about this problem is that Brian did such a great job of writing a question that merges the 3 topics that we talked about Tuesday, Wednesday, Thursday, all into this one wonderful FRQ. It's certainly a challenging FRQ, and if you wanted to really follow it to the letter of the law and really show tremendous notation, it's a little intimidating. And our wonderful partner Ted Gott did a fantastic job of detailing all of the minutia that really would be required if this were to be solved, in the world of academia and done so in such a way that it was communicated effectively. So let's take a look at this. We have an alphabet soup, so to speak, of terms: a sub n, b sub n, c sub n. Then we know that k is a constant that's either 1 or larger. And our part A says, let's consider this alternating series where a sub n is on top of c sub n, and k is equal to 2. We want to know what the series absolutely converge, conditionally converge, or will it diverge. So I'm just going to slide along with Ted's wonderful documentation. And again, these are available, or soon will be available, I should say, on the Dropbox site for today's particular lesson. So if you go ahead and take a look at this alternating series, we just assemble it by putting the a sub n term on top and the c sub n term on the bottom, and we start thinking about, okay, we got to figure out how this is going to work. We want to look at the absolute value of this nth term expression initially, so that we can make some kind of determination about its behavior. And once we do that, the alternating component essentially disappears. Now, I may have to do a little hand waving here because this n minus 5 is really causing us a lot of problems with this question. Because when n starts with 1, you can see how we're going to have some negative terms for a while, right? So that's something that we have to consider. It might be more appropriate. Maybe if I started this with n equals 6 here, it could be a little bit more, possibly notationally accurate. But we're going to go ahead and leave it like that, and we're going to go ahead and say, all right, what does this particular series do? Is there a test that we could use to determine its behavior? And from the lesson just yesterday, Ryan showed us that there's this wonderful thing called the limit comparison test. If we look at this guy closely, we can see that it somewhat resembles 1 over n, right? If we just kind of block out the terms that really don't mean much and then reduce, so that 1 over n then can be divided into that original summation, or that original nth term expression. So I take my original expression divided by what I'm comparing to, 1 over n, and I would take its limit as n approaches infinity. And once I multiply by the reciprocal and look at the fact that I have a degree of 2 for my n in the numerator and a highest degree 2 for my n in the denominator, we can just divide the coefficients, and of course we get 1. And that's a good thing, because if you recall, we want something that's nice and finite here, this result finite positive. So we have this one value that we can then construe. That is going to be opening the door for us to potentially have the same behavior. Well, what is that same behavior? Well, 1 over n we need diverges. So because we have this finite value for this particular limit expression through the limit comparison test, we know that we have to do the same thing, and therefore we diverge. So what does that mean? We've lost any chance of being absolutely convergent. That's all it means. We still could be conditionally convergent. So to check on that, we use the alternating series test. And this is where things get kind of interesting with this problem, because as you can see, this thing is kind of a hot mess for a while, right? By the time we plug 1, 2, 3, 4 in for n, we have this nice alternating behavior. But boy, when we plug n equal 5 in, then we get 0. So we kind of lose that nice alternating behavior with our signs. And what that's going to allow me to do is kind of think about starting the series at 6, right? Kind of like I indicated before. I know that the first 5 terms are going to add up to c, and that's what our solution guide here says. C is the sum of the first 5 terms. So we know that that part is nicely behaved and convergent. I'm now interested in seeing what happens from 6 to infinity. So we take a look at this and we apply the 2 criteria from our alternating series test. Criteria number 1, once again, we take the limit of the non-alternating component. That would be this expression here, and that limit does produce a 0. Check, right? That's a desirable outcome that we wanted. And then the next piece is that you observe the behavior of the a sub n plus 1 term in comparison to the a sub n. Remember, we want the a sub n plus 1 term to be less than the term that comes before it, which kind of says that this series is engaging in some of this non-increasing behavior, or we could say in this case it's going to decrease, as you're going to find out. So if we apply a function to this particular series, we're going to call this temporarily f of n. We know that this f of n is going to decrease at some moment. Why do we know that? Well, because we cheated, right? We took a calculator and we took the derivative of this function and graphed it, right? So the graph of f prime of n over here to the side, just a small snippet of it shows that this function f prime is going to lie below the x-axis by the time we get to around 12, actually just a little bit before 12 if you kind of squint at that a little bit. So what that means is from 12 on, we have this decreasing behavior that is abiding by that criteria that's set forth by the alternating series test. So if I let k now be the sum of the first 11 terms, right, which we know is going to be some finite sum, right, convergent, I can set that aside and then say, now this alternating series starting with 12 is going to have to converge because I met the 2 criteria. Wow, conditionally convergent. It's a tough problem. It's a good problem. That n minus 5, I think, is what really caused a lot of the headaches here. Okay, now luckily the last 3 parts aren't nearly as bad. I'm going to still go ahead and just highlight them here through Mr. Gott's wonderful solutions here. So let's consider the series here 1 over b sub n, where n starts at 4. Does this series converge or diverge? Well, we go ahead and assemble it by replacing the b sub n with what he's equivalent to. And then we look at this and say, hey, we probably could use one of our comparison tests here. It seems like the direct comparison test would be a fairly easy one, because if we compare this to 1 over the square root of n, right, because that's what this expression kind of looks like a little bit. 1 over the square root of n is divergent, right? It's a divergent p series. And more importantly, this 1 over the square root of n is smaller than the original 1 over the square root of n minus 3. Remember, when you have larger denominators, you've got, let me say that one more time, if you have a smaller denominator in the case of this n minus 3 under the square root, you're going to end up having a larger overall fraction. And because 1 over the square root of n lies in that divergent zone, if you remember Brian's graph yesterday, anything that's larger than him is going to also lie in that zone. Sometimes when I teach this, I use like an airplane analogy, like the 1 over square root of n is this airplane that's flying, and the 1 over square root of n minus 3 is this airplane. Make sure my hands can be seen here. So the airplanes are flying, and we have the 1 over square root of n minus 3 that's larger. Well, to diverge, that means that the planes are going up to the sky. Right? To converge, it means the planes are going to land. They're going to come to the ground. They're going to converge to the ground. There's a finite place that the planes can get to along the ground, right? They can't go underground. But if the plane goes up to the sky is infinite. So if we think about this plane at the bottom, right, the 1 over square root of n that's going to diverge, if he's always underneath the 1 over square root of n minus 3, he's going to force him to diverge as well. So it's another way that you can kind of work an analogy to understand the direct comparison test. So in any event, we see that we have divergent behavior in this case because of the conclusion of that DCT. All right, so looking at part C, consider another series S that's the summation starting at 5 of d sub n. And to complicate things even more, let's throw every single summation, or every single nth term expression into this d sub n. So we have a times b all over c. In terms of k, which series should be used with the limit comparison test? Well, let's first of all assemble the series. So we have our a times our b on top and our c expression on the bottom. We don't know what k is in this case, but if we just do a little bit of sort of mental kind of simplification here with this, if we focus on what is going to be the most important terms out of the numerator and the denominator, we can see that the numerator's degree is really going to consist of this n to the first times the square root of n, or an n to the half. That's all that really matters to us. I know you can't really multiply these two things together. You can't really boil those together, but if we think about what the behavior of the degree is, right, the exponent, we see that it's going to behave like a 3/2 power down the road. And down the bottom, you can certainly see that k is going to be that power of n in this case, and we're told that k is larger than or equal to 1. So that means that k has got to be the largest exponent, at least it's a tie. And then when we look at this, n to the 3/2 over n to the k, and simplify that by dropping the n to the 3/2 to the denominator, giving it a negative exponent, we can then consolidate that exponent and call it a k minus 3/2. Now what that means is that series is the one that we should use if we're doing the limit comparison test. And that's what the question was. What is it that you're going to compare this to? Now, because we don't know k specifically, we can't really move on any further with this. Now in part D, we're asked to find the smallest possible integer value of k, where s from part C will converge. So in this particular case, we know that our summation of 1 over n to the k minus 3 halves is going to be a p-series. Now how do we get that? We're going back to part C if you remember, so this is our answer that we had previously. And in order for that to be a p-series, and in order for it to converge, we need this k minus 3 halves being greater than 1. So we just simply add 3 halves over to the 1, and we get k is greater than 5 over 2. Now you have to be careful, because we didn't really answer the question yet. It wants to know what is the smallest possible integer value. So you have to think, okay, well, what's the next integer that's larger than 5 over 2, 2.5 in this case, and that gives us 3. All right, so let's go ahead and move on to our lesson overview for today. What we're going to do is introduce another very common series, the geometric series, and we're going to determine the conditions by which these series will converge or diverge. And then we're going to do something very interesting, something that we haven't been able to do here lately, and that is to discuss how the convergent geometric series can reveal the sum. We can actually add up an infinite geometric series and get an exact answer every time. Can't do that with too many other series. What you need to know, obviously, solid understanding of the concepts of converge and diverge. All these techniques for evaluating limit can come into play here, and we've already kind of talked about how we've used the alternating series tests a little bit. So we could have some application or some problems, conceptual problems that tie in some other ideas, and that's always a good piece of information to know. Another interesting problem here, what you'd be able to do, you're welcome to solve this on your own. It's kind of working with a famous fractal Kasha snowflake, which consists of infinitely many equilateral triangles. For each triangle besides the one in the center, the area is always 1/9 of the area of the next largest triangle in the fractal. So if the center triangle right here had an area of 1, what would be the area within the entire snowflake? The snowflake that continually morphs itself and adds more triangles around the edges. You can actually do that. It actually has a solution. All right, now if we start with our guided practice, I'm going to take you guys back to Monday. Do you guys remember Monday? Do you remember the lesson over 10.1? I think I was cutting up pizzas and cake, and now I'm hungry again. So if we recall our previous lesson about when we were cutting up pizza, recall that the pizza was cut into 4 equal slices, and I wanted to share those with Alicia, Ben, and Carlos. And then that leftover slice was then further subdivided into fourths again, and then each student would continually receive one of those new smaller slices while the leftover slices were continually subdivided over and over and over again. And we asked, how much of the pizza does each student end up receiving? And it was very easy to tell that when all was said and done, that every student was going to end up with a third of the pizza, right? Even when I take this last little morsel of the leftover piece and continually to subdivide it, it's going to seemingly look like it's disappearing because the pieces get smaller and smaller. But what we noticed was that each person was initially receiving 1/4 of the total pizza, and then the next slice that was laid on top was 1/16, and then 1/64. Well, what we notice here is that there's a common ratio, right? What is it that you would do to 1/4 to get to the 1/16? And that is simply multiply by a quarter. And you can see how that's very consistent, right? That's extremely important. We have to have that consistent ratio. Otherwise, we do not have a geometric series. All right. Now, we knew that the sum of this was going to be 1/3, right? Just by common intuition. But here in a little bit, I'm going to talk to you and introduce a formula that you may have already seen possibly in a previous class that will allow you to determine how we get this 1/3 without having this visual representation. Okay? So we'll get back to that in just a moment. But for now, here is our formal convergence criteria of your new geometric series. And the geometric series may have the look summation a times r to the n, where n starts at 0. I don't want to mislead you and make you think that you always have to have your geometric series starting with an index of 0. That's not true. I've looked on my shelf. I have 12 calculus books on my shelf, and 10 of them show this formula. The other ones show a formula that's slightly different. They start with n equal 1, at which case if this n was made to be bigger, then that r would just be ratcheted down just a notch. So it's very likely that in your textbook or in the notes that you have from your teacher, maybe this is the formal presentation of a geometric series. It doesn't matter. Right? We can start at n equal 5, and we can still construe convergence and divergence by using the same technique. So basically, if you look at that common ratio, which is called r appropriately, if the absolute value of that is less than 1, that's strictly less than 1, then we have a convergent series. Now, on the other hand, if the absolute value of that r is equal to 1 or larger, then we are going to diverge. So it's a really quick, what sometimes we call an eyeball test kind of test, because you can just immediately look at that r and make the determination. But you're going to have to be careful, because sometimes you're going to have to simplify things to get that r in the form that you want. So let's take a look at our first example in our guided practice here. For each of the following geometric series, find the value of r and determine if the series converges or not. So in this first one, we have our summation n does start at 0, moves up to infinity. We have a 4 constant out in front. That's not going to have anything to do with the convergence, right? It's a factor out to the front. And we have 2/3 as our r. So we want to notice this as the r value, okay? Now, I wouldn't worry a whole lot about this n-1 in terms of figuring out convergence. That n-1, it could be a little problematic if we were actually finding the sum of this, and we're going to talk about that in a little bit. But if you've got this form here and you are very confident that your r value is 2/3, you can then look at that and say, okay, the absolute value of that r is 2/3. We know that that is less than 1, and then you can make the determination that the series is going to converge. It's that easy, all right? Taking a look at part B. Now, part B's got a little bit more going on, so we might want to kind of doctor this up. We might want to simplify this just a little bit. So I'm going to rewrite this summation where n starts at 0 and goes to infinity. And then what I'm going to do is, especially in that denominator, that e to the n plus 1 bothers me just a little bit. So I'm going to bust it apart. I'm going to use some properties of exponents that will allow me to call this e to the n multiplied by e to the 1. We saw Brian do this earlier in the week. You're basically working backwards with your property of exponents. Whenever you multiply like bases, you can add the exponents. We're just working in reverse. Now, why is this important? Well, the pieces of this, and I'll highlight them here, the pieces of this that don't have an n exponent attached to them are really not going to have a big role in determining our convergence. They're just going to be a constant. So I could rewrite this one more time, right? If we rewrite this where I extract the 3 over e in front, so it's sort of playing the same role that the 4 played in part A, and then 2 raised to the n over the e to the n could very cleverly be written as 2 divided by e, all raised to the n power. Now I've got a very recognizable r value in this problem. Well, the r is equal to 2 over e, and because it's positive, I don't have to worry so much the absolute values. It's not change that. Now, it will be very important here to understand that e in this case is certainly a number, right? We don't like to use e as a variable when we get to higher level mathematics, and it's very important that you have a rudimentary understanding of that e is approximately 2.71-ish, okay? Just like pi is about 3.14. Those kinds of things are very helpful to know when you're dealing with not just geometric series, but a lot of times power series use e and pi to sort of disguise the placement of what you would normally see as nice numbers. So if you know that e is 2.7, 2 over 2.7 is definitely less than 1, right? So we have another convergent series on our hands here, guys. All right, let's take a look at part C. Now in part C, it's pretty clear that you have an alternating series, and it's easy to think, oh, now I have to use the alternating series test with this. Well, you could certainly try to use the alternating series test, and I would like you to maybe use some time to kind of investigate that on your own. It is a lot easier if you think about this as a geometric series, however, because if we rewrite this, kind of like we've been talking about before, that 3 in the denominator is not being affected by any exponent n. So we could just bring a 1/3 sort of in front of our expression as such, and now we have this a value as depicted in our formula, right? And then the r to the n is right there. So we know that the r is -1, right? Well, we know that the absolute value of that needs to be strictly less than 1 in order to converge. Well, if we take the absolute value of that r, that's obviously positive 1, and that meets the criteria of being greater than or equal to 1, which is our second criteria, or our second keynote here in our convergence test, and that says that we would have to diverge. Okay. There's several other problems here in this guided practice. I'm going to leave D for you to take a look at, and if you have your document, you'll notice that there's an E, F, G, H, and we're not done yet, an I, J, and a K that follows. Now, I would like to talk just a little bit about I in this case. I, J, and K are a little different in that the series is kind of presented in a more open form. We don't have that summation notation expression, and a lot of students think, oh, well, does that mean I have to rewrite this so that it is in a summation form? Well, it really depends on what the question is asking. If we are only concerned about finding the value of r and determining convergence or divergence, we could do that fairly easily without having to rewrite it. So in this case, if you think about, well, what is it that needs to be done to take a 4 to become a -2? What kind of factor, what kind of multiplication do you have to invoke here? And if you think about that for a little bit, well, we're definitely making it smaller, so we're probably multiplying it by a fraction. And for it to get to 2 is taking half of it, right? And the r value is certainly going to have to be a negative number in order to invoke that sign change. So it looks like our r would be -1/2, right? And you want to make sure that that continues, and it does, right? If we continually multiply by -1/2 from one term to the next, and then the absolute value of that r, of course, is +1/2, which in this case is certainly less than 1. So we have a convergent series on our hand here. And you'll really do part j and k in a very similar fashion. All right. Now let's get to the good stuff. This is the really neat stuff. We talked about how you can actually add the terms of an infinite geometric series, and it's likely, depending on the state that you're in, depending on the curriculum that your school uses in pre-calculus, you may have been exposed to this just a little bit. So that's great that you can tie in those ideas from an older course. But it says if you've got an absolute value of r that's less than 1, and therefore a convergent geometric series, the sum of that series can be written as taking the a value and dividing it by 1 minus r. Now I want to make sure that we define very clearly what is this a value, because that's where a lot of the deception lies. I know that in this form you're saying a right there in front and saying, oh, well, there's my a value, I'm going to use that no matter what. You've got to be very careful, especially if this n starts with something besides 0, especially if this r to the n might be written a little bit differently. You want to make sure that you just don't willy-nilly think of a as being what's present in the summation. You want to think of a as just being the first term of the geometric series, and you're always going to be able to figure that out by plugging in your very first index, right? In this case, it would be 0 for that problem, all right? R is still going to be that common ratio, but I advise you again that you're going to want to simplify like we did in the previous problems, okay? Now, if you allow me just really quickly to go back to the pizza question, I'm just going to go back on the slide or so here, and remember that we knew that the sum was going to be 1/3. Well, we know that to be true because the sum of this convergent geometric series is the first term, 1/4, all divided by 1 minus the ratio, which coincidentally is 1/4 as well. And if we simplify this just using some very basic arithmetic, 1/4 over 3/4 is, I know you guys know this at this point, the 4s are going to end up canceling out, and there's your 1/3 that you can get using formula, all right? So let's take a look at some problems that deal with finding the sum of an infinite series. So this would be example 2 in your guided practice section. So we've got determine if the following geometric series converge or diverge, and if the series converges, find the sum. Well, I guess we don't really know if we have convergence or divergence, so we ought to take care of that first. So you're going to tackle this problem kind of like we did in example 1 first. So we could rewrite this a bit. Let's see, we have a 2 that sort of acts as a constant, doesn't have an exponent n attached to it, so maybe I bring it to the front like that, and then I have a 1/4 to the end that we could cleverly write as 1/4 all raised to the n. Right now we can get by with that because the numerator is 1, and 1 to the n is still going to be 1 no matter what. All right, now I think we've got a good form. We also have a convergent series, right? R is certainly equal to 1/4, which is absolute value 1/4 less than 1. So we know that we converge, and it's only because we converge that we can actually find the sum. Now the sum here could be done in a very quick manner in that you can use the 2 as your a and the 1/4 as your r. But just to verify, if you were to let n equal 0, let's say we go back even to this term. If n were 0, 2/4 to the 0 is 2/1, which is 2, and that reinforces the fact that our first term is definitely going to be 2. Our a value is 2, and then we divide that by 1 minus 1/4, and we get 2/3/4. And I think if you multiply by the reciprocal, we're going to find that we get 8/3. So there you have it. If we take 2/4 plus 2/4, let's start with n equals 0. If we take 2/1 plus 2/4 to the first, plus 2/4 to the second, plus 2/4 to the third, and we keep doing that forever, we will converge upon this finite sum of 8/3. Let's take a look at part B. Really like part B. Part B's got a lot of crazy things going on with the pi and the e. Once again, I think you're going to want to simplify this just a little bit. It doesn't quite have that form that we want. So what we'll do is we'll rewrite. Notice how this series starts with a lower index of 2. Right? There's a reason for that. Pi to the n stays in the numerator, and for this denominator, I'm going to call this e to the 2n. And then since I have a -4 there, what I could do is think about this as a division problem. Right? I could divide that denominator e to the 2n by an e to the 4. Okay? Again, I'm just using that subtraction of exponents rule in reverse. When you divide like bases, you subtract exponents. Now, if I multiply by the reciprocal here, what is going to happen is that I'm going to see an e to the 4th up here, say maybe out in front of my expression, and then I have a pi to the n over e to the 2n, and this is where we got to be very careful. My goal would be to write this expression with a single power of n. What do I do about this 2 times n? Well, again, I'm just thinking about another rule for exponents, and that is whenever you have a power raised to another power, you would multiply those, right? That's how I got that 2 times n. Again, I'm just working that in reverse. So now I can see that my r value is pi over e squared, and that makes you think about all sorts of things. So pi over e squared, well, pi is 3.14, we talked about that. E is 2.71. Now, if we square e 2.71, we actually get a number that's pretty close to 10. In fact, I think I talked about that a few videos ago. So we end up with a very larger denominator, I guess I should say, than we do a numerator. So we could say that this r, which is pi over e squared, is indeed less than 1, therefore we converge. And unfortunately, I've used up all my space, so I'm going to have to work down here a little bit. I apologize for that. So for the sum, I just need to find out, well, what is the first term? I wouldn't leave it to chance. I wouldn't just assume that e to the 4th is your a. It very well might be. I think it is. But let's plug 2 in just to make sure. And I might just do that at the very beginning, right? And I end up with e to the 4 minus 4 on the bottom. That's e to the 0, which is 1, right? Well, wait a minute. No, let's think about this. If I use this very first expression, I'm not going to get the same a sub n because this first expression was not simplified. I don't want to use him. What I want to do is I want to use this guy right here. I want to use the most simplified version of my series to extract my information, all right? So if we take a look at him and we let n be 2, what we end up finding out is that our first term would be, if n is going to be 2, did I double check in here? Let me write what I got for my solution and see if this is correct here. If I let n be 2, my first term is going to be, I have to work this out to the right here, e to the 4th times pi squared over e to the 4th. Those cancel, and I get pi squared. So my first term is going to be pi squared, okay? And then in the denominator, I have 1 minus, and then my r value is pi over e squared in that regard. And you know what I think I'm going to do is probably leave it like that. You could multiply through by an e squared if you wanted to clean this up. I don't know if it cleans it up all that much because it is still pretty nasty, but if I multiply through by an e squared, I can write the final answer like that, right? Apologize for that. I had to hesitate here a little bit because this a value, this first term, certainly wasn't going to be this guy, and it really was very necessary for us to use n equal to in this particular expression. Now, if we would have used this, now if I go back to this, I might need to kind of clean this up a little bit. I believe that we could have used this as well, all right? My original key had a slightly different answer, and I got kind of scared there for a second. So if we would have used n equal to at this point, pi squared would have been our a value. So, all right, let's take a look at C and D are a couple of problems that I'd like you guys to try on your own, if you wouldn't mind. As are E, F, and G. I think those are very similar problems that just kind of build on some of these concepts. And then let's talk just really quickly here about A in part 3. I'm not going to solve it for you, but I'd like to get it started. It says find a geometric series whose sum is represented by this repeating decimal. Well, what you're going to do here is we're going to call this 0.54 repeating, 0.54 plus another value that would put a couple of zeros as placeholders for that initial 5 and 4, and then we'll plop another 5 and 4 down after that. And then if we continue to do this, and it's likely that you may have seen these in a pre-calculus class, we could do this forever and ever and ever, and that will produce this repeating decimal 0.54 repeating. Now I want you to look at this and determine whether or not this is a geometric series. And it turns out that it is. And I would like to even push the boundaries of the directions and have you guys go ahead and solve this. I think that would be great. Go ahead and see what is the fractional value that this series would add up to. And you'll notice that in the key, we present the problem just like that. So A and B are really good problems here in example 3 to kind kind of tie this into really a basic type of number theory question. All right, the check for understanding consists of two wonderful practice problems that we are going to assign for homework. They're wonderful questions that start to invoke the idea of a power series to a degree, but you are, in this particular case, you have this unknown value of k. And in part A, we ask that you find that value of k such that the summation is equivalent to 3. In part B, we ask you find that value of k so that the summation is equivalent to 4/3. And in part C, we say, well, there is no k, so that the summation is going to equal to 1, but you have to explain why. You have to show why. So it uses the same idea of the sum of an infinite geometric series, s being the first term over 1 minus r, but just in a slightly different environment forces you to find that value k. And there's two different versions of this. So if you have a little bit of trouble with practice 1, you can check the key. Don't look at practice 2 solutions, but then learn from your mistakes and then try this practice 2 and then check the answers on the key to see if you did a little better. Debrief and summary for today. Well, what do we do? Well, we applied our enduring understanding again that limits will always allow us to determine the finite sum of infinitely many terms. That's an overriding theme here this week. Our key takeaways is that geometric series is a series with a constant ratio between its successive terms, and that the standard way of maybe presenting one of these is the summation of a times r to the n, where n starts at 0 and goes to infinity, will converge if the absolute value of that r is less than 1. And then we know that the sum of this convergent geometric series can be written as a over 1 minus r, where a is the first term, r is the common ratio. There are lots of misconceptions and errors that students can make. Two of the most common ones, be sure to simplify or rewrite those exponential expressions for determining what your r value is and whether or not your series converges. You saw that happen quite a bit in our examples. And the use of the formula for the sum of a convergent infinite geometric series does not require that lower index to be 0. Just be sure that the value of a is the first term. And another one that I didn't write in here, but you have to be very careful, because if you have a divergent geometric series, nothing is going to stop you from trying to use that formula, a over 1 minus r. It will produce an answer. It will be a wrong answer. So you have to know to not use that summation formula, a over 1 minus r, unless your ratio is less than 1, or the absolute value of your ratio is less than 1. All right, the AP exam practice problem is another fantastic one, a 3-part problem here that does a great job of leading into Brian's discussion on power series and the interval convergence on Monday. But you're going to be given this particular series with this unknown k, and you're going to be able to find the value of the series when k is 1, find the value of k if that series is equal to 12, and knowing that that series converges when k lies between a and b, you're going to be able to find out what the a and the b values are. So it's a wonderful problem to lead into that. I promise you we're going to have a real quick field trip here. So in lieu of our Twitter shout-outs, I want to kind of share an experience that I had a few years ago. I was very blessed in the summer of 2016 to travel to Europe to investigate the birth of calculus. I had been so enthralled by the story of Newton and Leibniz that I'd spent 3 years researching it heavily. I read 7 different biographies of both of those particular mathematicians and wrote up a proposal, and I was very fortunate to be able to win and go and take my family with me. And the trip began in London, which is the hotbed where Newton spent most of his adult life. But what I wanted to do is just take you on this little field trip here up to Woolsthorpe Manor. Now, to set the stage here, young Isaac Newton was in his 2nd year in Cambridge, and Cambridge, obviously a very popular institution of higher learning in England, still in service today. And he was holed up there at Trinity College there in Cambridge. And at the time, Europe was under the siege of a plague outbreak. And it wasn't the first time. It's kind of ironic that we're kind of not dealing with so much plague, but this COVID-19 is certainly on our minds. But back then, it was a common occurrence. Europe didn't mess around anymore, right? When they went through the big plague, the Black Death, which basically led to the Dark Ages, they wanted to make sure that they were prepared, and so they were very good at exercising social distancing, right? So basically, all of England closed down, Cambridge shut down, everybody had to go home. And so young Isaac Newton, at around age 21, found himself going back to his boyhood home of Woolsthorpe Manor, which was just about a 3-hour carriage drive, horse ride north of Cambridge. Now, while at Woolsthorpe, a lot of really amazing things happened. So we're going to talk about here. But I'd like to give you some pictures. And right here is the exterior shot of the home that Isaac Newton was born. And this house was built about a century and a half before Newton was born. This is in the late 1665 is the time that Newton left Cambridge to go back to his home. It was on a farm that was pretty much renowned for herding sheep. At a young age, Newton, when he was born, his father had passed away prior to his birth, and his mother had raised him for a few years. But then his mother met someone else, ended up marrying a local pastor, and ended up being basically the stepmother to his children because he had lost his wife previously. And I know that sounds terrible for his mom to leave him and live in another home, but it wasn't really all that uncommon at that point. And young Isaac went ahead and stayed at this home, and he was essentially raised by his grandmother during the time. Well, anyhow, as an adult, Isaac would retreat back to this home, and I'm going to give you a little bit better view here of the front entrance. And one of the things that people are going to always note here is, wow, look at those. What the heck? Is that like some graffiti? Is that spray paint? And what that is looks like an integration symbol, of course, but those symbols were part of that home long before Newton was born. Those symbols are basically iron beams that sort of reinforce that second level. And the big irony to this is that symbol is not even a symbol that was instituted by Isaac Newton in the first place. It was definitely one of his I don't want to use the word enemies, but one of the other founders of calculus. But it's very, very serendipitous that symbol is used and it appeared on Isaac's home his whole life. Right up here is the room where it happened. And we're going to take a little bit closer look at that room here. Here's the interior of that room looking out that same window. Yes, that is an apple tree, right? Is it the apple tree? Well, there are lots of stories about the apple tree being in Cambridge. There's lots of stories about this apple tree. Agronomists have basically determined that the bark on this tree, the tree itself, is a descendant of a tree that certainly lived there 350 years ago. But in this room is for the most part where a lot of the foundations of the calculus that we study was first discovered by Isaac Newton. There's a table right by that window that has an array of papers. Those obviously were original manuscripts. They're reproductions. The desk is a reproduction as well. They feel like from a lot of the information that they gathered, this was very similar to the desk that Isaac Newton would have written upon. Those particular papers actually list his sins. Isaac Newton was a very religious man, and he would write his sins down every week. So I can just imagine him sitting at this table during the outbreak of this plague, kind of developing some ideas that led to his reflections, which are what we call derivatives now, possibly looking out that very same window. Right? And kind of close this out. This is the tomb of Isaac Newton after, of course, he died in Westminster Abbey. This is probably a little scary to show this because I'm not really supposed to take pictures in Westminster Abbey. So that we see to the left is a wonderful monument that's devoted to him, probably one of the most ornate monuments in all of Westminster Abbey. And then to the right is sort of the slab along the floor where about 8 feet under that rests the remains of Isaac Newton. And we can see that this is written in Latin, which was the common way to depict tombs of dignitaries at the time. This bag here, what this bag is basically, I always give my students at the beginning of the year, as soon as they answer the first question, a little band that has name of our school colors with 80 capitals written on it. And I always take I took a whole batch of them with me, several hundred of them, and I actually took them into Isaac Newton's chamber. I got permission to rub them on his walls. I was a little scared that I was going to have a restraining order on it, and I actually took them to his tomb as well. And a lot of teachers around the country that I do workshops for like this idea, and I tell them if you buy your own bands and send me an email, I will send you one of the bands that has Avon High School on it with Newton's aura, and you can mix it with your bands you distribute to your students, and we have the Newton aura going right now. We might want to hold off on that right now under the current circumstances, but later on when things settle down, that's certainly something that we can try. A little fact about Newton before we close out: Isaac Newton spent the last part of his life as the head of the Royal Mint, and there's a problem in Europe with people clipping coins. Clipping a coin is basically taking a knife and shaving off the outside edges, and coins at that time were precious metals. That's how they had value, silver, gold, and people would sliver off just a little bit of silver on the coin, put it in a drawer, and the coin would still have the same value. But this posed a big problem because as that silver stockpile kind of grew, they could cash that in, and enough people doing this, it can really flood the economy with money and causes inflation. That's a big issue. And so Newton wanted to put an end to that, and he was actually sort of part of a team that made a decree that people could be executed for clipping coins. And it's because of his work there with the Royal Mint that if you take a quarter out of your pocket and look around the outside, it has those ridges, and those ridges are there so that we can tell that people didn't clip the coins. So he had a lot of really interesting impacts into the world of economy in that regard. So anyway, I hope this was a little bit of a nice excursion for you you. I always enjoy sharing this with people. It's one of the criteria of having received the grade that I always try to share this knowledge with students, and it's great to kind of understand a little bit of the history of how calculus developed. It's really a soap opera when you look at what happened between Leibniz and Newton, and I certainly would encourage you guys to read up on that. But once again, we always want to make sure that there's proper access. So if you are having trouble, or if you have a friend that's having trouble getting online, especially before the AP exam is coming up, make sure that you reach out to the College Board at cd.org/tap, and they can get you certainly squared away. Certainly enjoy today. I want you all to have a great weekend. You deserve it, and we're going to come back Monday with a great lesson from Brian. So we'll see you then. In the meantime, we definitely want you to stay safe, stay healthy, and keep learning.
Calculus. Dealing polynomials. Infinite series. Differential equation. Calculus. Dealing polynomials. Infinite series. Differential equation.
Well, good morning, everybody, to Monday's edition of AP Calculus BC Live. I am sitting here live in the set. If you recognize it behind me today, this is the set of the TV show The Office. I mentioned last week that I'm an obsessed fan of The Office, so I thought it would be only fitting today to use that as my background, because we're going to see several Office quotes throughout the presentation today. Once again, thank you to the talented Kate Gavin for our intro music. It's really hard, by the way, to listen to that in the beginning and not start dancing, but I realize my webcam is on, so I want to dance for everybody and mortify those of you watching, most importantly, mortify my own children. We begin today at topic 10.13 in the curriculum, and if you're like me, that doesn't really mean much to call things by number, so 10.13 is talking about radius and intervals of convergence of power series. In case you're new here today, hope you do this again. In case you're new, my name is Brian Passwater. I'm a high school teacher at Speedway High School, and last week I shared with you the tattoo that I got on my arm last year, my one and only tattoo of the zeta function. My wife calls it my friend finder because if anybody recognizes it in public and knows what it is, so I meet new friends. Needless to say, my mental list, my circle of friends is pretty small at this point. I also want to share a couple more things, so we're going to see some of these more this week. In the bottom corner, these are two of my cats, a brother and a sister. They're kind of posing with their arms out there. They're pretty camera photogenic, I think. We've got some more cats and some other animals. My wife and my children sort of buy animals and bring them home, and then I find out about them later, so I'm not really sure at this point how many animals are in my house. I know we have a third cat somewhere running around and a couple other things as well. And then the other side of the photo here are my adorable little children. They're much older now, they're in high school, but next to them is our dog Buddy there. They're holding him. He was just a brand new little puppy, and I wanted to show a picture of Buddy because you're going to see him today later on in the lesson. But also on Wednesday, I'll be back. Tomorrow, Tony's going to talk about ratio tests. It'll be a really good, powerful lesson that we're going to need for this year's exam. But on Wednesday, I'll be back, and we're going to attempt to clone my dog Buddy on Wednesday. So hold out for that on Wednesday. We're going to attempt to clone my dog live here on AP Calculus BC Live. So don't forget to be here Wednesday at 9 a.m. Eastern time to see if we can successfully clone my dog. You've heard us say this multiple times, but in each one of these videos, in the bottom in the comment section, there's a link. And if you click on that hyperlink, you will go to the Dropbox folder that Isaac Newton has made specially for you. And that's where you're going to be able to get the handouts and all the materials we do during these lessons. So we really recommend, if at all possible, to get those materials, print them all prior to the lesson. That way you can follow along with the problems with us. And one of the things that you're going to notice if you download those materials is that we have way more problems on the handouts than we could possibly do in one of these lessons. Tony and I are the optimists. So we always think we're going to have all these examples. We're going to be able to get through a whole bunch of examples. At the end of each lesson, we're like, wow, where'd the time go? There's so many more examples of problems that we wish we could have done. But we purposely write additional ones that you can do on your own practice. And then each evening, each night, we will post the keys for those in the Dropbox as well. That way you can check your work. And they're not just keys, but they're really detailed solutions that our friend Ted got types up. Thanks to Ted once again. You can follow along with your work and compare your work. And if you're stumped on something, it'll really show you the algebraic way to progress and solve some of these problems. All of the problems that you see on these lessons are unique. They're new. They're questions that I've written specifically for these lessons. And so, last Friday, Tony talked us through a little bit about what this new exam this year, this unique exam is going to look like. We already knew there were going to be some topics not on the exam. Then on Friday, the College Board released some more information about it. So what do we know? We know it's going to be a 45-minute exam. We know there will be no multiple choice, just two free response questions. The first one is going to be 25 minutes long, so it's a little bit longer than we're used to for an FRQ. And the second one is going to be 15 minutes, kind of what we're typically used to in the past. That's it, two FRQs to assess all the things that we've learned or should know from Calc AB and Calc BC this year. And so one of the things that Trevor Packer mentioned and College Board mentioned as they've talked about this new exam is they said on this new exam, they're writing it with the understanding that students are going to have calculators. They're writing it with the understanding that you're going to have technology with you. So it's assumed to be open book or open notes. It's assumed that you might be using a calculator, but they want to be able to write questions. They're not going to go just look up an answer in a book. They're going to be able to write questions where you can't just Google something. You can't just ask somebody quickly or have a way to cheat or something like that. They also want to write questions where you can't just type the answers in your calculator and get the answers immediately. Well, how are they going to do that? Well, I know for one thing, the College Board is very good about writing questions and writing exams, and they're going to find ways to do that. And so all the questions that we're writing in our lessons are designed to give you ideas or examples of how that might possibly look. Now, full disclosure here, Tony and I are just regular classroom teachers, just like the other teachers across the country. We have no special insight. The College Board doesn't tell us any secret information because we're doing these videos for you guys. We are equally as anxious and equally as uncertain what this test is going to look like as everybody else, but we're trying our best to prepare our students for whatever this test might look like. And so the questions that I write that we use on here in our activities are kind of our best guess, our best ideas of how we prepare kids for what this exam might look like. So really take time to try some of these problems because I really think if you do these problems, it's going to help you get as fully prepared as possible for this year's exam. We've been asking you to tweet out if you're an AP student what you love about your AP Calculus teacher, or if you're an AP Calc teacher watching these videos, tweet out what you love about your students. And whenever you tweet out, make sure you include the hashtag AP Teachers Rock or AP Students Rock. Today's tweet for AP Teachers Rock: thanks Dr. Gupta for your dedication to our BC class. You inspire each of us every day with your engaging lessons. Can't wait to get back to school with you. Hashtag AP Teachers Rock. And then our AP Students Rock tweet of the day: my AP Calculus students are amazing people. I can agree with that. I'm so proud of how hard they work and how much they care for one another. Hashtag AP Students Rock. Thank you for sending those tweets out to us. And if you have a Twitter account, don't delay today. Hop on Twitter today at some point and tweet out what you love about your teacher. Tweet out what you love about your AP students. Don't forget to include the hashtag on there because this is how we're searching those tweets to find something to share each day. So if you tweet out today, come back and check to see whether you made the tweet list. Upcoming lessons. Well, this is the last week of new lessons. This idea we're teaching new content. So we're going to be talking about the radius and interval of convergence today for power series. This is not one of the asterisk topics, meaning it's not going to be directly tested, but two comments I want to make about why you should still watch this video. Don't turn it off right now. Number one, there's a lot of office quotes today. That's pretty awesome. So make sure you stay tuned for that. But it would be a real shame if you made it through Calc BC and didn't have at least some exposure to power series. They play such a really pivotal, important role in Calc 2, and it would be really hard for me to let you go through a whole year of calculus, even under these circumstances, and not at least have some exposure to power series. Because even though it's not tested, they really will tie a lot of things together and bring things together that are tested. And then finally, it's important because, like I mentioned a second ago, we're going to be bringing in all these things that we've done so far that are tested today. So we're going to be talking about a new idea, but we're going to do it in context of a testable idea. And by the end of the lesson, we're going to be tying in things and reviewing the topics that are tested on this year's exam. Tomorrow, Tony's going to kick us off with the ratio test. It's our last test of convergence that's tested on this year's. We'll spend a couple of days with Taylor Polynomials approximations. On Wednesday, that's where we're going to try to clone my dog Buddy. He's cute enough to be worthy of cloning. Don't tell anybody we're going to try to clone an animal right now. And then Friday, we'll end up our Unit 10 discussion with alternating series airbound. And that's the title of the topic, but we're also going to be tying in, once again, all these ideas that are tested in this good comprehensive question review for the AP exam. And then starting next week, beyond this week, we're going to be doing some AP calculus exam prep and review. And so the great Michael Scott once said, I understand nothing. If you feel that way right now, if series is feeling a little bit overwhelming, or calculus or calc C is a little bit overwhelming, you've got the point that you feel like you understand nothing. Tune in each day this week, and especially tune in for this review prep, because we're going to take you from understanding nothing to making you feel like you are ready to tackle the AP exam and just crush it this year. So stay tuned for those review lessons. At the end of each lesson, Tony and I give you an AP practice exam problem to try, right? Those are unique questions, and I'm writing these questions to give you a glimpse of maybe how AP problems might look on the exam, right? How can we test you on something knowing that it's open book or open notes? How can we kind of test you on something knowing you might have a calculator or Google and really still see whether you understand the ideas or not? And that's where those AP practice problems come from. At the end of each lesson, we give you one, and then at the beginning, our warm-up is just to go through that. So I would encourage you, if you haven't been doing it, take 5 or 10 minutes to try those AP exam practice problems, because that really is going to be good practice for the exam if you do those each day. So this is our problem from Friday that Tony left us off with. Instead of the geometric series, he taught us about geometric series last Friday. The series k times quantity k plus 3 over 6, all to the n power. And then part A wants us to find the sum of the series when k is 1. Part B, find the value of k such that the sum equals 12. And then finally on part C, that series converges between A and B, but it diverges at A and at B. Let's find those values of A and B. So let's see if we can solve these problems together really quickly. Part A says, let's find the sum of this when k is 1. So really, they told us that k is 1. So if I plug in 1 for k, I get a 1 here in front, and then plug in a 1 for k here, but 1 plus 3 is just 4, right? And 4 over 6 is going to reduce to 2/3. And we know, hopefully remember from Friday's lesson, that geometric series, as long as our ratio, the r value, is less than 1, the absolute value of r is less than 1, then this geometric series converges. Well, in this case, our r value is 2/3, and 2/3 is certainly less than 1. So we know that it converges. And geometric series are really unique because it's the only series that we really have learned so far that not only can we figure out whether it converges or diverges, we can actually figure out what it converges to, right? We can actually figure out what the sum is. Whereas the other series, when we did alternating series test, or we did p-series, right? Maybe the ratio test tomorrow. When we learn these other tests, we could figure out whether they converge or not, but yet we never knew what they converged to. The geometric series is pretty powerful because it actually will give us a sum. And we learn that if a geometric series converges, we know that the sum is going to be a over 1 minus r, where a is the first term and r is that ratio. So in this case, our first term, if you plug in 0 for n, you get 1 times 2/3 to the 0 power. So our first term is just going to be 1 over 1 minus r, and we already have said our r is 2/3, so it's 1 over 1 minus 2/3. And if we reduce that, 1 minus 2/3 is 1/3, and that gives us 3. So when k is 1, the sum of the series is going to be 3. For part B, now it's the same idea, right? But Calc works good about writing questions, and reverse things around at you a lot, right? Making you think about things inside out, working things frontwards and also working them backwards. And so here, telling us the sum of the series equals 12, let's figure out what k is. Well, we know again, a geometric series converges, it will converge to a over 1 minus r. Well, if this sum equals 12, then it has to converge, right? Otherwise, you wouldn't have a sum. And they're telling us the sum is 12. So in this case, instead of telling us what k is, they're telling us what s is, and we're going to hopefully work backwards. And so we know that the sum is 12, and then a is our first term. Well, how would we get a? We would plug in 0 for n. When we get our first term, anything to the 0 power is going to be 1, and 1 times k in front is just going to be k. So our first term is k over 1 minus r. And what's r? Well, this is our r value right here for geometric series, and we get r is going to be k plus 3 over 6. And now we have an equation that we can solve, and just kind of back to basic algebra. There's a lot of different ways we might solve this equation. For me particularly, I like to multiply by 1, and I like to multiply by 1 by multiplying by 6 on top and 6 on bottom in this case. And so on the right hand side, we multiply top and bottom both by 6. And so I get 6k on the top and the bottom. For multiply by 6, we're going to get 6 minus the quantity k plus 3. I got rid of that complex fraction that we had there originally. Notice I put the k plus 3 in parentheses because this has to be distributed. And so this gives me, use a little arrow here, 12 equals 6k over, this is if I distribute this minus sign here, it's going to be 6 minus k minus 3, which becomes 3 minus k. And now I can multiply both sides by this 3 minus k to get rid of the fraction. If I multiply by 3 minus k, we're going to get 36 minus 12k equals 6k. And then a little bit of solving here, and we're hopefully going to agree that our k value is going to have to be 2, right? And we have to be careful because we want to make sure that, in fact, this doesn't contradict anything, because remember, the only time we're allowed to use this series formula for geometric series is if the series converges, right? If our r value, if the absolute value of r is less than 1. So I got a k value. Let's double check now, make sure it wasn't some kind of extraneous association. So if k is 2, then our r value in this case would have been 5 over 6. And that is less than 1, so we know that we're okay. So our k value is going to be 2. And then finally, in part C, we know that this whole thing converges when k is between a and b, but it diverges at a and b. Let's find out what a and b are. Well, remember, a geometric series converges when the absolute value of r is less than 1. Well, another way of writing that, to solve an absolute value problem like this, that's equivalent to saying that r is between -1 and 1. So if this is our r value here, we can say that -1 is less than k plus 3 over 6, which is less than 1. And now we're just solving this compound inequality. Multiply everything by 6, and we get -6 is less than k plus 3 is less than 6. Subtract 3 from everything, and we get -9 is less than k is less than 3. And there we go. There's our a and b values. We know that at 3 and -9, the series diverges. We can quickly check. If k is 3, this r value here becomes 1. And if r is 1, a geometric series diverges. And if k is -9, we get -1 inside of the parentheses for r. And if r is -1, the geometric series also diverges. And so in this case, a is going to be -9, b is going to be 3. There we go. There's our solution to last week's AP practice problem, which is our warm-up today. So let's talk about what we're going to do today. Well, we're going to introduce the idea of radius of intervals of convergence with power series. We're also going to, probably more important for you right now, is we're going to connect and review the different series that we've talked about so far. We'll put all these together. Most of the lesson today, we're connecting to the geometric series that Tony talked about last Friday. But then at the end of the lesson, we're going to connect to all of those previous series. So what should you already know how to do? Well, hopefully you can solve an absolute value inequality. That's what we just did on the last part of that warm-up. You remember a little bit about geometric series when they converge, the alternating series test for convergence, our p-series and when they converge, as well as our nth term test for divergence. All those previous things that we covered in previous videos are going to be brought together at some point during today's lesson. And by the end of the lesson, we'll be able to solve some of these really kind of cool problems, some problems that I don't think you can just solve on Google or a book, where if you're given a geometric series like this, what is the smallest possible sum for geometric series? And so by the end of today's lesson, hopefully we'll be able to apply the things that we learned to tackle a problem like that. So guided practice is kind of like the notes of the lesson, right, each day. So here's where we're going to start. I'm going to tie this back really briefly to what we did on Friday, just to make sure we're on the same page. We're going to extend this here to today's lesson here in about 30 or 45 seconds. And so consider the geometric series 4 times 1/3 of the n power. Does the series converge or diverge? Well, we know it's geometric, right? So how do we know it's geometric, first of all? You know, the dead giveaway for geometric series is when the exponent is to n, right? That's how you know something's geometric, is when the n in the problem, the variable of the series, is an exponent. That creates a geometric series. And our geometric series will converge if the absolute value of r is less than 1. Well, in this case, r is equal to 1/3, and the absolute value of 1/3 obviously is less than 1. So this series will clearly converge because it's a geometric series where r is between -1 and 1. Well, let's extend this to be a little bit more broad. Instead of calling it 1/3, we'll call it c over 3, where c could be just different various numbers. And let's figure out whether this converge or diverge for different values of c, right? And so what if c was 2? Well, if c was 2, that means that r would have been 2/3, right? And the absolute value of 2/3 is still less than 1, which means if c was 2, the series would still converge. But what if c was 3? Well, if c was 3, then r is going to be 3/3, and the absolute value of 3/3 equals 1. And the geometric series will only converge if the r value is strictly less than 1, right? If it's positive. So in this case, it equals 1. This would be a really good example of a divergent geometric series. And we can keep going through these different values, but it's kind of leading us to the idea of, instead of checking individual numbers, we're more interested in knowing what are all the possible values of c, right? We know that c would converge if c was 2, it would diverge if c was 3. We can kind of quickly mentally check that if c was -1, it would converge, but yet if c was -4, it would diverge, and if c was 0, I would claim that this converges. Okay? And so we have these different values and different kind of ideas to figure out how they converge or diverge. How would we list them all out? Well, first of all, there's an infinite amount of possibilities. We're not going to list them all out one, but could we list an interval? Is there a way to describe all the values of c that would make this series converge? And that brings up two interesting and important concepts in calculus. One of them being this idea of intervals of convergence, meaning what are all of the values of c that would make that series converge? And then secondly, this idea of a power series. Power series are pretty important ideas in calculus. We're going to introduce it a little bit today, but we're not going to go into a whole lot of depth because we're going to reinforce it more tomorrow with the ratio test, and we'll reinforce it more with our Taylor polynomials on Wednesday and Thursday as well. So I just want to introduce it mainly to connect it to our understanding of geometric series. So the definition of a power series is x is a variable. So now what we're doing is we're creating another variable in the problem. So instead of having chosen n in the problem, we're going to have an x and an n. And so a power series is a series where it's a sub n, x sub n. You can see the expansion here, where you have a sub 0, x, sub 1 of x, on and on, going on. That's all a power series. And it looks kind of like a polynomial, doesn't it? Think about what we talk about with polynomials. A polynomial, you're in algebra, right? Might look something like, 3x squared minus 4x plus 1. That's a polynomial, right? Well, here's the main difference. Number one, with polynomials, when we were in algebra, we started with the largest exponent first, right? To put it in the standard form, and we kind of went down from there. Well, a power series is going to start going up. And the reason why it's going up is because a polynomial has a finite number of terms, whereas a series has an infinite number of terms. Keep getting bigger and bigger and bigger and bigger. So we can kind of think about a power series as a polynomial that just keeps going and going and going and going and going. A polynomial kept going and getting higher and higher powers of x. We do that indefinitely. Turn into what we would call a power series, right? You think, well, how is that possible? How could you have an infinite number of powers of x have to be meaningful? How could that actually be anything? How could that equal anything? Well, that's what we've been doing, haven't we? We've been looking at all these series so far, and we've learned that we can have an infinite amount of terms, but yet the series can still converge. Even though we're adding an infinite amount of items, it won't go out of control or bounce back and forth sometimes. It'll converge to a specific value. In the same sense, a power series, for certain values of x, even though we're adding up an infinitely amount of them, it still converge to a very specific value. And then a more general case of a power series is going to be a power series centered at c. It's the exact same idea. Instead of just x, we're going to have x minus c in place of all the x's. And we would say this power series is centered at c. And so we're going to talk more about this a little bit more today. It looks a little overwhelming at first, but it actually ties in really well with what we've been doing already with geometric series. So we're not going to spend too much time today on the background of power series. We're just going to kind of throw it out there. We're going to do some stuff with it, and we'll formalize it more later on. But we do want to connect it and make some parallels to our idea of geometric series from last week. So our geometric series from last week, a r to the n power, would just create this series. Now, if we let every r become x in this geometric series, if I just replace all those r's with x's here, we get this. And that looks a lot like what we had up here, doesn't it? It's basically a geometric example of a power series. Now, geometric series can be an example of a power series. There's other types of power series that we're going to learn about. The geometric one's a really good example to help us kind of solidify our understanding or start to play around with power series a little bit today. And we knew for a geometric series that as long as the absolute value of r was less than 1, then the geometric series would converge. Well, if we're going to replace r with x, that means for our power series, for this example at least, we need the absolute value of x to be less than 1 to guarantee convergence. Now, tomorrow, Tony's going to get us into the ratio test. We're going to learn there's some other types of power series that we can look at that aren't going to be strictly geometric. And so this reasoning that we have that absolute value of x has to be less than 1, this is going to be a condition for geometric power series in particular. So as the great Michael Scott would say, I don't come up with this stuff, I just forward it along, right? So I didn't create power series. I'm just going to be the person that's going to pass along these ideas to you today. So let's look at some examples here. So consider the series x over 4 to the n power. For what values of x will this series converge? Well, first of all, we see it's geometric, right? Because the n is the exponent. Whenever you see the n as the exponent, you know it's a geometric problem. So even though there's an x in the problem, I don't have to let the x confuse me at first. I always think easiest for me to look for the n first. And n is only exponent in a series problem. It gets me into the mindset of it's a geometric type of question. And a geometric question tells me that it will converge as long as the r value, in this case x over 4, as long as the absolute value of that is less than 1. And so writing our inequality, we know that -1 is less than x over 4 is less than 1. Multiplying everything by 4 on this compound inequality, we're going to get -4 is less than x is less than 4. So what values of x will this converge? It'll converge as long as x is between, and not including, between -4 and 4. I'll let you try example 2 on your own after this video, but I want to get you some more interesting examples as well as some vocabulary that's become pretty important. So there's 3 really big words that are going to play a big role with power series, and even with Taylor polynomials later on, we're going to have the idea of a center, idea of a radius, and the idea of an interval of convergence. So a lot of vocabulary words that can seem a little bit daunting at first, but here's what they mean. And I think we use some examples, it'll really solidify how to tie these ideas together. The center of a power series is the x value, it's the location, the x coordinate, where all the terms except maybe the first term are going to be 0. Okay, and every single power series will converge at its center. Okay, so the power series, the center of it is going to be the x value that makes all the terms essentially just become 0. The radius of a power series is the distance, right? Think about radius of a circle. You start at the center of a circle, right? We have a center here as well, and on a circle, the radius for the center is how far you can go in each direction until you get to the boundary of the circle. Well, for a power series, it's very similar. We start at the center, we know the series converges, and then from there we can extend out in each direction a radius, a certain amount, and we know that that radius, the series will still converge as long as we're inside of that boundary. If we go beyond that boundary, beyond the radius and the outside of it, then the series will diverge, right? And so the radius is how far we can go from the center and still have a convergent series. Sometimes the radius is 0, meaning it only converges at the center. Sometimes the radius is a finite number. You can go like 3 in each direction or 5 in each direction. And then sometimes the radius is infinite, meaning no matter how far you go away from the center, the series will still converge. And we'll see examples of all 3 of those, especially tomorrow in our unit on the ratio test. And then the interval of convergence is just a complete interval. It's all those x values that will create a convergent series. On the last example, our answer, that was the interval of convergence. The interval of convergence is just basically the solution. What are all the x values that would create a convergent series? And so in our initial discussion of our geometric series, we talked about if we replace r with x, we get this geometric power series, right? And we know that this converges whenever the absolute value of x, as x was our r value, was less than 1. And that means that -1 is less than x is less than 1. So if I think about this, it means this is going to converge anywhere between -1 and 1. Well, what's in the middle of -1 and 1? Well, 0 is right in the center of that. So 0 would be our center. And then from our center, we were able to move 1 unit to the right and 1 unit to the left. That is our radius of convergence. So this is our interval of convergence, -1 to 1. Our radius of convergence, which we use as a capital R, very different than the little r we use for geometric series. The radius is going to be 1, and then our center of the series is going to be 0. That's kind of a quick example of a basic problem. Let's take a look at an example where it's not going to be quite as straightforward as that, but you're going to learn pretty quickly that finding these 3 ideas is actually pretty easy, and they're really well connected. So once you understand what one of them is, it will help you find the other one. So let's find the center, radius, and interval of convergence of this geometric series. Notice the n is an exponent, so I know it's going to be geometric. And because it's geometric, I know that the absolute value of r in this case, which is x plus 1 over 5, has to be less than 1, right? Because it's geometric. Now, I keep bringing up this idea that n is the exponent, so it's geometric, meaning meaning I'm able to use this little shortcut here because the examples we're looking at are geometric. Not every example is going to be geometric, right? There's more series, there's more power series, especially besides ones that are simply geometric. So these are nice examples to get us started with this because all the examples we're doing are geometric. Well, tomorrow with the ratio test, we're going to learn how to do a similar idea with series that are not geometric. So be careful of that. Don't just assume we can always apply this technique. This is working because we're dealing with geometric examples. So for solving this, we already said that we know we can write this as a compound inequality, right? -1 is less than x plus 1 over 5 is less than 1. And then to solve this, I can multiply everything by 5, and we get -5 is less than x plus 1 is less than 5. And then subtracting 1 from all sides, we're going to get -6 is less than x is less than 4, right? And so if I think about this on a number line, here's -6, here's 4, and I know that my series converges between those values. So the interval of convergence, we're going to read the IOC right now, the interval of convergence is going to be -6 to 4. I'm using parentheses because we're not going to include the endpoints of a geometric series. It's possible it wasn't geometric that the endpoints could be included. And then I have to also find the center and radius. Well, if I have -6 and I have 4, the center of those two values, let's right in the middle of -6, 4. Well, mentally we can kind of figure out that it's just -1, right? So the center is going to be -1. And then the radius is from that center, how far could we move in each direction, right? How far are we able to go in each direction from the center? Well, if we're starting at -1, we can see that we were able to move a distance of 5 in each direction, right? And so our interval of convergence was -6 to 4, the center was -1, and the radius was 5. Now, looking at our initial problem here, you can kind of realize that a lot of these numbers, like the center and the radius, they seem like they're connected somehow to the original ratio, right? Initial little r value for a geometric series, and they are. So let's talk about how that connected. Kind of an easier way, I think, to find the center, radius, and interval convergence is to think about this form right here. That we're solving for these things. If we can get our problem to a form, we have the absolute value of x minus some value or plus some value is less than some other number. Then this value that we're subtracting here, we're going to call it c, that's our center. And then the value that we have over here, once we get it in this form, is going to be our capital R or our radius of convergence. So we can find our center and radius really quickly, actually. And then from there, we can find our interval almost immediately. So let me show you a couple of examples of how using this form can help us avoid using those compound inequalities. And so let's find the center, radius, and interval of convergence of this geometric power series. It's geometric again because the only case of n of the problem is an exponent, which makes this a geometric type problem. And so since it's geometric, we know that the ratio x minus 4 over 2, the absolute value of that needs to be less than 1. So what are we trying to do? We're trying to get this into this form. So instead of writing a compound inequality like we did in the last example, is there a way to make this look like this? And to make it look like this, really what we want inside the absolute values is just x plus or minus the number. We don't want to have any multiplication or division. So to make it look like this, we can multiply both sides of the inequality by 2, right? And so we're going to get the absolute value of x minus 4 is less than 2. Multiply both sides by 2. And now look, we have a form that looks like what we have here. Once we have it in this form, we can immediately conclude that the center is going to be 4. Remember, the center is the x value. That will make all the terms become 0, right? So x is 4, then everything inside of here becomes 0. And we get a whole bunch of zeros repeating, right? And so our center is going to be 4. Then the other side, once we get in this form, is going to be our radius. Our radius is now 2. Big R is 2. So we've already found the center and the radius. How can we use that to find our interval of convergence? Well, all we have to do, I like to make a little number line. It helps me think about this pretty easily. The center is 4. That's the center of our power series. And the radius is 2. Remember, the radius means how far you could go from the center in each direction. I can move 2 to the right and 2 to the left, which means this is going to go to 2. If I subtract 2, it's going to give me just a 2. There shouldn't be a negative there, sorry. And then on the other side, if I add 2 to this, it's going to give me 6. And so my interval of convergence, my complete interval, is going to be the open interval from 2 to 6. So let's try another example here. We can kind of take it even one step further. For what values of x will this series converge? And on top of that, what is the sum of the series for all those values of x? Well, first one, it says for what values of x will the series converge? That's just another way of asking for the interval of convergence. So how do we find the interval of convergence? Well, the same way we just did. We would say the absolute value of x plus 2 over 3, and we know that has to be less than 1 because it's geometric. And we want to get it into this form. We're not dividing or multiplying by anything. And so we would take this and then multiply both sides of the inequality by 3. And now by looking at this, we know the center is going to be -2, right? Because it's -2 plus 2 would give me 0. And then our radius, or capital R, is going to be 3. So using our number line again, our center is going to be -2, and we're going to move 3 in each direction, which means if I go backwards 3, I'm at -5. If I go forwards 3 from -2, our center, we're going to get 1. And so the x values are going to be any x value between -5 and 1. So that answers the first part. What values of x? Well, the values of x for x is -5 and 1. And then what is the sum of the series for those values? Remember, the sum of a geometric series is just going to be a over 1 minus r, where a is the first term, r is the ratio. Well, a, the first term, is what we would get by plugging in this lower bound for n. So if n is 0, we get x plus 2 over 3 to the 0 power. Well, anything to the 0 power is 1, and then 1 times 4 in front is going to give me 4 for my first term, and then over 1 minus r. And r in this case is going to be just x plus 2 over 3. This is our sum. We can leave it like this. We don't have to simplify it. Basically, for any x value between -5 and 1 that I plug in here, I know the sum would equal whatever this is if I plug in the same value x, right? This form that would only work for x values that are between -5 and 1. All right, so a couple things, putting it all together for us today. Going back to what we've learned before, right? The nth term test says if the individual terms of a series do not approach 0, then we know the series diverges. If the terms do approach 0, then we don't know, right? It's inconclusive. We have to use another test. The p series test from last week is when n is the base, and we know that n is the base. P series will converge whenever p is greater than 1. Geometric series, we talked about Friday again today, is AR to the n power, and that will converge when the absolute value of little r is less than 1. And not only does it converge, it's the only series so far that we're going to talk about that we actually know what the sum of the series is. And then our alternating series test from last week says if a series is alternating, it will converge if two conditions are met. Number one, the limit of the terms approaches 0. It has to pass the nth term test, basically. But also the terms have to be decreasing at some point on. And so this is Michael Scott quote. There's a lot of office quotes I think that really are apropos for what we're doing in Calc. He says, and I know exactly what to do, but in a much more real sense, I have no idea what to do. Is that ever you where you feel like you understand the topics in Calc, you understand series and convergence, or you think you do, then it's all mixed together. You're like, I know what to do. When it's all mixed together, I feel like I have no idea what to do. And so one little tip that I'll give you, my dog Buddy here, who's got smart glasses on, I'll give you a little tip here. He'll always say, this is my dog here, he'll say, find in. I think a really good way to start these problems when you're overwhelmed is to find in the problem. Kind of like find Waldo. Where's Waldo books. I was gonna have a nice picture of Where's Waldo, but I'm pretty sure that's trademark. I put it up here on the screen. It could be booted off of YouTube forever. So I don't want to do that and risk getting in trouble. But find in the problem. And so for what we're doing, especially this year, there's a couple of examples. If n is the base of the problem, right? It's a base. Then we know it's a p series problem. If n is the exponent of the problem, then we know it's going to be geometric from Friday. And then a third case would be what if n is a combo of those two, meaning it's a base and it's an exponent, or what if it's just something different, meaning like what if you had n factorial, or what if you had n squared and then 3 to the n, where it's both a base and an exponent. It's a combination of things or something different. That's what we're going to look at tomorrow. And that's going to be a really good example of when we use the ratio test. But I think a really good first step when you're putting all these together is to find n in the problem. If n is a base and only a base, think p series. If n is an exponent and only an exponent, think geometric series. And if n is a combination of things that has different rules to the base, but it's also an exponent or it's got a factorial, something kind of weird going on with n, think about the ratio test. And so if you think about where n is first, I think it's going to help you have a better idea of what to do on these problems. And so I know we're short on time here, but I want to give you a chance to put this into a little bit of practice here. And so we're going to find the center, radius, and interval of convergence for this series. And so I want you to try this. I know I have the timer here, and the timer says 2 minutes. I'm going to put it down to 1 minute, but I'm not going to give you a full minute because we only need a few seconds. So see if you can try this right now. See if you can do it on your own. It's a really important step is to see if you can do this I'm going to put the timer on here. You want to get about 30 seconds. I'm going to play some nice music that Kareem should share with us. Awesome, thank you, Kareem, for that. So let's go ahead and see how you did on this problem. Find the center, radius, and interval of convergence. Well, before we just talked about, we knew this is geometric, right? And so it's going to be the r value, little r, is the absolute value of x minus 4 over 6. That needs to be less than 1 for a geometric series to converge. And if we multiply both sides by that 6, right, we get the absolute value of x minus 4 is less than 6. And since we're in this form that we are kind of wanting, we know the center is going to be 4 from here, and big R, the radius of convergence, is going to be 6 right here. So we got the first two figured out. And then the interval of convergence, we just start at the center of 4, and we know we can go 6 in each direction. So 4 plus 6 will be 10, and then 4 minus 6 is going to be negative 2. So our interval of convergence is going to be negative 2, 10. Let's refresh what that means, right? What do I mean by interval of convergence? That means you can plug in any x value you want between negative 2 and 10. Any number you pick between there, this geometric series would converge. And anything that you pick beyond those numbers, including negative 2 or 10, this geometric series would diverge, right? So we're finding all of the values where the series would converge. In the handouts in the Dropbox, you're going to see some additional problems, right? And I kind of skipped to practice 3 here to give you an example of what it looks like. The series 2 times x plus 3 over 4 to the n power has interval of convergence a to b. Find the limit as x approaches a from the right-hand side of the series. Now, Kelly Kapoor would say from the office, I have a lot of questions. Number one, how dare you? This is how my students, I think, look at me when I ask them questions like this, right? We give them kind of a simple example. Oh, I get this isn't so bad. And I throw a problem like this on there, and I'm like, how dare you ask me that problem? Well, here's what I want to tell you about problems like this. These problems have a much worse art than they do height, meaning they look a little bit scary on the surface. But if we understand the idea behind series, these problems actually aren't that bad, right? Notice I tell you it has an interval of convergence. Well, could we find the interval of convergence? Sure, we could. And then once we find the interval of convergence, we now know what a is, right? And then the second part is find the limit as x approaches a from the right-hand side. Well, of course, x has to approach a because we can't converge at a. Remember, on a geometric series, the endpoints will not converge, so we can get closer and closer and closer to a. So as x gets closer to a, let's find the sum of this. So once we know what a is, we can write an equation for this sum. We did that in one of our examples, find the sum of this. And then all we're going to do is find the limit of that as x approaches that value a. So I'm going to leave that one for you, but you're going to have some nice worked out solutions. So this is a good example again of how can the College Board write questions? How can we test you on this exam when we know you're going to have notes or Google or other things available to you? Well, questions like this would be a really good example of. I'm just going to Google a problem like this. It's a little bit more abstract, a little bit more conceptual to get to the heart of whether or not you understand these ideas. You can't just Google something and look up an example in your book, right? And so a couple other ones that we're not going to look at, I want to point out to you is going to be now we're connecting some more ideas together, right? For which integer values, that's key, do both of these series converge? Well, what do you notice about this problem? I'm thinking the first one here, notice the n. Remember I said the first step on a series is find n. Well, the first series n is here, and n is an exponent, right? And if n is an exponent, that means the problem is geometric, right? And if it's geometric, now we know that the r value, which is this, needs to be less than 1. And we can solve this and find the interval of convergence. Well, on the second example, again, let's find n. Well, n is here. N is not the exponent now. N is now the base of the problem. It's not an exponent at all. N is the base. And if n is the base of a series, then that means it's going to be a p series, right? And for a p series will converge if exponent, in this case 2x minus 11, is greater than 1. And we can solve that inequality. And we solve both of these inequalities. We're now going to try to find an overlap, right? And so this is a good connection between things we've done before as well as things that we're looking at now. As a chill treat for you, I create these activities called Big Tens. And Big Tens are things you may have done if you're a student, you may have done in your class, your teacher may have shared them with you. If your teacher may have seen them on the Facebook group, or if you've been in my workshops, you certainly have seen them. I create these Big Ten activities where you're going to see a box at the top of the page and you're going to see the numbers 0 through 9. And there's going to be 10 questions, right, that go along with the activity. And each question should have an answer 0 to 9. And it should be a whole number 0 to 9. So it kind of gives you a built-in check to make sure you're on the right track without just giving you the answers. And so if you get an answer, for example, of like 11, well, you know you made a mistake. That's not a number between 0 and 9. Or if you get a decimal like 1.5 or 3/4, you know you made a mistake. That's not a number between 0 and 9. Every answer should be a number 0 to 9. And if you do it correctly, you will get all 10 numbers crossed off. And you have to be careful on these because I purposely think about what are the big mistakes, what are the big misunderstandings and misconceptions that students make on the exam. So I purposely will write questions that check for that. And so if you get 5 for an answer, you cross off 5, you're feeling pretty good about yourself. And all of a sudden, 4 problems later, you get 5 again, and you got 5 twice. That can't happen. You know you made at least one mistake, right? If you do it correctly, you use every number exactly once with the 10 questions and you cross them all off. So you're going to see a large variety of problems. Some are a little more easy, some are a little more challenging, more conceptual, but they're going to give you some good examples of whether or not you're ready for this year's AP exam. So this is just a little snip of the activity. There's question A, D, I, and J here to kind of share with you some of the different level questions, right? So this is a brand new one, by the way. So this has never been seen before. I'm giving it just to you right now. I feel like one of those telemarketing guys on those commercials, right? If you order right now, you get this for free. This is free for you. It's in the Dropbox. The whole activity is for students and teachers alike. A couple of snippets of the types of questions that you might see. How many of these series are conditionally convergent? So what I've done is I've combined all of the series that we've talked about so far, all the lessons in Unit 10 that Tony and I have addressed or taught are going to be in this Big 10 activity. Just the things we've learned so far. Nothing else beyond this or before this. Just what we talked about in these YouTube live lessons. So how many of these are conditionally convergent? Which of the following series diverges by the nth term test? For which value of p would both of these series converge? Find the value of k. So sum of this equals 2. So if you've been listening to these lessons and doing the problems with us, you've seen problems like this in each of our lessons, and now we're going to have a chance to put it all together. So here's a snip of what that activity looks like, but the whole activity is in the Dropbox. I'll show you a key in there for you as well by this evening. So let's do a little bit of debrief and summary as we wind up here. Today we talk about a couple of things using limits to help us determine a finite sum for infinitely many terms using geometric series. And we talk about power series a little bit, right? So we didn't go super depth behind the theory behind power series, and we're going to keep building on that in the next couple of lessons. But we're going to hopefully give you a better understanding of power series as we talk about ratio tests and polynomials and Taylor series that are on this week. Be really careful. We have 2 different r values now, right? With geometric series, we have little r, which is going to be the ratio, and we have this big R now that we're talking about power series, which is the radius of convergence. They're not the same thing. Be careful about using lowercase and uppercase and what those 2 things mean. So your AP exam practice, which Tony will do tomorrow as his warm-up, it's a good one. If you have a chance, you can watch this and take a photo of it. But again, it's in the materials in the Dropbox. If you have it printed off, you can find it. But it'll give you a good way to tie what we did today, as well as what we've done in previous lessons. And then this part C is really a good question, I think, because it's going to tie into what Tony's doing tomorrow. We'll see how many you can extend your understanding of what we've done so far to part C. So give us a chance. It should only take you about 5 or 10 minutes to kind of think about this. It's not very algebra heavy. It's more conceptual understanding. So try that and see how you do tomorrow. And Tony will walk us through this and see how we did. A quick reminder: the College Board is very aware that not everybody has access to technology or ways to get to these AP live videos or even the AP classroom problems, or maybe you're concerned about even taking the AP exams online this year. So they want to make sure that everyone has the resources they need. So if you or somebody you know might have an issue with technology, please share this website cb.org/tech and make sure that everybody has the resources that they need. So I hope at the end of this, as Calc says, guys, I'm like really smart now. You don't even know, right? After these lessons, you guys are really smart now. People need to understand how great you are. So thank you so much for tuning in today with us. I hope you'll stay with us tomorrow as Tony goes into the last convergence test, the ratio test. I'll be back here on Wednesday as we try to clone my dog Buddy, because the world needs more buddies in this world. Have a great day, and we'll see you tomorrow.
Good morning, everyone, and welcome to AP Calculus BC Live. We're so glad that you decided to tune in today and join us with our lesson that will cover the fourth and final convergence test that we're including in our virtual lesson package. That would be 10.8, the ratio test for convergence. And as I'm sure that you're aware by now, students will be taking a rich version of the advanced placement exam this particular year, next month. And many of the topics from this final unit, Unit 10, over series convergence and the behavior of Taylor series will be omitted. So we'll talk a little bit more about that in detail, but it's nice that your focus is a little bit more narrowed and you're only going to be responsible for the 10 convergence tests. As always, we would invite you guys to download the PDF file for today's lesson and begin to work the problems as we work them with you. Those files can always be found in the description located beneath each video. Once again, if you don't know already, my name is Tony Record. I'm a calculus teacher at Avon High School in Avon, Indiana, just west of Indianapolis. And I would like to take a quick opportunity to recognize a couple of colleagues who have really made it very possible for me to balance the demands of two somewhat hectic schedules at times working with AP Live and my own particular classroom. And that would be, first of all, my principal, Mr. Matthew Shockley, and along with assistant principal, one of my assistant principals, Mr. Matthew Hines, who oversees the mathematics department at Avon High School. I just really appreciate their tremendous generosity and patience for allowing me to miss morning meetings at times and just to catch up with them later on in the day. So definitely, gentlemen, thank you very much. And I'd also like to give a shout out to another very important person, a lady by the name of Dolores Record. That is my wife, who has really been able to do a wonderful job of putting up with my hectic schedule, who will allow me to invade her workspace here every other day so that I can broadcast and connect wired to the internet to give you this high quality, fast, hopefully internet fast lesson every day. So what we're going to do here is talk just a little bit about our upcoming schedule. As you can see today, we're going to hit this ratio test. And then moving into the next couple of days, we're going to spend some time talking about these Taylor approximation functions. And that will take a couple of days. Brian's going to do a great job of introducing it tomorrow. I'll piggyback on that particular concept on Thursday, and then we'll close out our new material Friday with the alternating series bound in topic 10, 12, and then all the fun starts. Next week, anticipate Brian and I probably working together online, kind of going back and forth, taking care of a lot of really wonderful free response question practice review over some various topics. We're going to start with some BC topics, as you can see next week, and then we'll kind of spill into some of the AP topics that you had learned more towards the beginning of your year. Because you're probably a little worried, right? You're a little nervous that you may have forgotten those. Well, don't worry. We're going to make sure that we go over those with a fine-tooth comb. And by the time you finish that 3-week review cycle, we're going to get you guys ready for your advanced placement. We mentioned this already a little bit Friday, and Brian did again yesterday, but the exam for this year has changed a little bit. The date for AP Calculus BC would be Tuesday the 12th, so you definitely want to mark your calendars for that. It will consist of 2 free response questions. We know the first one would be a 25-minute question with a 5-minute upload time, and at that point you would have access to question number 2 and have 15 minutes to answer that with a 5-minute upload time. You can certainly use keyboard to answer your answers. You could also take photographs of handwritten work and then send it to your computer before you upload it. But we'll talk a little bit more in detail about this as we get into our review session. But we certainly wanted this to be on your radar. So with that, let's go ahead and take a look at our warm-up. This is the AP review question that Brian finished his lesson off with yesterday. A wonderful question that sort of begins to open the door to the topic that we're going to talk about today. So we have this series, a sub n, as n runs from 1 to infinity, and it's defining a sub n as x minus 3 over quantity to the nth power. In part A, we're defining the center and radius of convergence for that particular series. And in part B, we're going to modify that series a little bit by applying a coefficient of 6, and then state that x is going to be 1, and ask to find that summation of 6 times a sub n. And then in part C, we're going to introduce yet another series. And we're going to say that it's known that the summation of a sub n over n, as n goes from 1 to infinity, has the same center and radius of convergence as our original summation of a sub n. We're going to ask you to find the interval of convergence for that new series, a sub n over n. So with that, we'll dive right into this. And in part A, finding the center and radius of convergence for the summation of a sub n. Well, we look here immediately and we see this a sub n has this component of x minus 3, and we can always look there to figure out where we're going to be centered. So we think about what value of x would allow that to take on a 0, and that's where our centering is going to occur. It doesn't take a whole lot of effort to see that you're centered at 3, right? You should really never have a lot of trouble figuring out where you're going to be centered. Okay? Now, for the radius of convergence, there's really a couple of ways that you can do this. One way is to understand the fact that this is going to behave as a geometric series, right? That piggybacks a little bit off of the topics that we talked about at the end of last week. So therefore, we know that the absolute value of x minus 3 over 4 is going to be less than or equal to 1, right? Again, this has that geometric look to it. It has this value that we can construe as r, our ratio raised to this power n. And because by virtue of this 4 being positive, the absolute values really don't have much of a role there, so we could go ahead and just multiply both sides by 4 and land here. And once we get there, we talked a little bit about yesterday about this value to the right of this inequality sign can serve as that radius. And a lot of times they denote that radius with capital R, and as we said, that would be 4. Now, another way that you could verify this, if you want to go ahead and actually solve this for x, you would then apply the opposite of that 4 on the left side, drop in your x minus 3 there in the middle of your inequalities, and then you add 3 to all 3 sides, and you have something like this. Now, the problem didn't ask for this interval of convergence. We're certainly going to get into that today, and that was a very big part of Brian's lesson yesterday. But you can see that the span from the left side to the right side is 8 units, right? And if we cut that in half, we're going to get that radius value of 4. All right. So if we move on to part B here, we have this brand new series in town, 6 times a sub n. But we have some other information. We are told that the x value in that series is going to be a constant 1. So we don't have this notion of a true power series that's going to have this x that varies from time to time. We have our sort of nice, normal, well-behaved series where we replace this x with 1, 1 minus 3, of course, is negative 2, and let's go ahead and reduce the negative 2 over 4 is negative 1/2. So we have that 6 in front, followed by this negative 1/2 to the nth power. And it's pretty easy to get lost in this problem and kind of think, well, what is this problem asking? It just says find the summation. So we have to kind of link that with the idea that that means that we want to find the sum. We want to find this infinite sum of the series. Well, wait a minute, there's not very many series that allow you to add an infinite number of terms, right? Geometric series is just one of them, and it's the main one that we're going to be talking about in this year's exam. So we have to realize that this has to be summed, and therefore it must be geometric. So we could call this equal to s like we have before, our sum, and we just apply our formula. And the formula, as it was introduced last week, a over 1 minus r, may not mean a whole lot. A lot of times you might question, well, what is this a? And we always encourage you to think about a is the first term, okay? So if we let n equal 1, we have 6 times negative half to the first power, which of course is going to be a negative 3. And then we can apply 1 minus the r, and the r in this case is negative 1/2. Now the r that I'm referring to here means radius, right? The r I'm referring to here is not radius. Sorry for the confusion. It means ratio, the ratio that's used in this geometric series. So we simplify this, and 1 minus negative half is going to be 3/2. And by the time we multiply by the reciprocal, we will have a sum of negative 2. And if we move on to the last part, it is known that the summation a sub n over n has the same center and radius of convergence as the summation of a sub n. Find the interval of convergence for this new series. So what I'm going to do first of all here is let's define the series a little bit more specifically, right? We know that the a sub n was x minus 3 over 4 to the nth power, so I'll start with him. And then we're going to divide this all by n, okay? X minus 3 over 4 to the nth power, sorry. And we're going to divide this all by n, which, I think for organizational purposes, if you would allow me to, maybe I'll write it as multiplying by 1 over n. It's the same thing. And we know that we have the same center and radius. So what that means is The center is still 3, the radius is still 4. So if we want to think about this visually, we have this nice center right here, 3. And with a radius of 4, that means we could go 4 units to the right, which would take us to, I believe, 7. And if we go 4 units to the left, that would take us at -1. And now what we have is our nice little interval here. This is our nice pseudo interval of convergence. Now, why do I say pseudo interval of convergence? Well, that's where the door is going to open a little bit wider to what we're trying to do in finding an interval of convergence. We have to make some determination about what the behavior at the endpoints are. We're very, very clear that in between -1 and 7, we have this wonderful convergent behavior, this absolutely convergent behavior. But at the endpoints, we're not quite so sure. So all that we have to do in this particular problem is test each of those endpoints into that original series and determine the behavior. So it doesn't matter which one you check first. I'll go with the one that's on the left. So that would be checking -1. And we physically replace the x that we see with the -1. And upon doing so, we would have the summation from 1 to infinity of -1 minus 3 is -4. -4 over 4 is -1, still to the nth power times 1 over n. Now we want to be able to draw upon some prior knowledge from last week. And we want to be able to recognize that the series that we're looking at now has a very special name. It's an alternating series, of course, but even more specifically, it's the alternating harmonic series. And we hopefully remember that the alternating harmonic series does converge. Now it converges conditionally, but that's good enough for us to include -1 in this interval. So we know that we have conditional convergence by virtue of this being the alternating harmonic series. All right, so we're going to include this -1. All right, now we're going to do the same thing for our 7. And so as we check our positive 7, we find that the series that we are creating, 7 minus 3 is, of course, positive 4. 4 divided by 4 is 1. So we have this 1 to the nth power, which I'm going to write down there. But if you think about it, it really doesn't matter what the power of n is, right? 1 to the second, 1 to the third, 1 to the millionth is still going to be 1. So all that we have here is the series 1 over n, which hopefully we will recognize as the divergent harmonic series. And that means that we will not include 7. All right. Now I wouldn't leave it the chance to just rely on that number line to express or convey what your interval of convergence is. I would rewrite it, and you can rewrite it whether you wanted to use interval notation. You could say something like bracket -1, comma 7 with a parenthesis. Another way to do this, so that we don't misinterpret brackets and parentheses, we could use interval notation and then thus underline the inequality around the -1. So that would take care of our interval of convergence. And you're going to see that we're going to revisit that idea, checking those endpoints quite a bit in today's lesson. All right, looking at our overview today, we are going to introduce another very common and I'm going to say a very powerful convergence test, the ratio test. You're going to find out that this test really takes care of a lot of our ills. It takes care of a lot of really nasty things that we might see in a series. And a lot of times, students might use the ratio test as like a go-to test when some of the simpler tests might still work. And that's fine. It might take a little bit more effort, but it is a test that does find itself working quite a bit of the time. We're going to also determine intervals of convergence for a power series. You've already seen us take care of that in more. And then we are going to review each of the infinite series convergence tests that would appear on the 2020 BC exam. Because as we check those endpoints, we might find that we have a P series with a geometric series or what have you, and we have to rely on those to tell what those conversions are. So of course, what we need to know, solid understanding of the concepts, convergence, divergence, techniques for evaluating limits are going to be very, very important for power series. Procedures for solving an absolute value inequality play a role, and we need those understandings of the convergence criteria for the P series and the geometric series that we just talked about. And then basically an understanding of comparison tests, because sometimes those will kind of find a way to weave themselves into some of these solutions. So an example of a problem that may have occurred maybe on some of the multiple choice type of items that you'd seen in some preparation materials for the AP exam. We got 3 series here. Notice all 3 of them have some very different qualities going on, and we would just simply say, hey, well, which of these following series would have an interval of convergence from -1 to 1 inclusively? In other words, we include those 2 intervals, and the ratio test would really do a good job of these. All right, so with the beginning of the lesson, we're not going to mess around. We're going to dive right in. We're going to show you what this ratio test is. And I say that the topic 10 introduces this. It's one of the most powerful convergence tests. And the reason why it's so powerful, it really allows you to test many types of series where other tests would really be problematic. So we have the series A sub n, consists of lots of non-zero terms. If we go about taking the limit as, and I think I may have a bit of a typo already that we need to fix here. Let's say that n approaches infinity here. I don't want to get you all confused. All right, so let's say we take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. And if that were going to equal some L, right, it's going to equal some numeric value, a number. We can then look at that L and make some determinations. If that limit's answer is less than 1, so it's a number less than 1, then we know that that series will converge absolutely. If that limit is equal to 1, then that says that this ratio test is going to provide no conclusive information about the convergence or the divergence. Well, there's obviously a third possibility, and that is if that limit is greater than 1. Well, what's going to happen there is that the series is going to diverge. Okay, so you have your 3 different possibilities. You can be less than 1, equal to 1, or greater than 1. Now, there's a second little caveat here. And again, I want to make sure that we make this change. Let's let that x be an n. So if we take the limit as n approaches infinity of that same absolute value of that ratio, and let's say that that tends towards infinity, well, then that means that that series is going to diverge. And a lot of people kind of wonder, well, really, what's the difference between these two? Well, they really have the same conclusion. It's just that I don't want to get us confused with a numeric value that's greater than 1 versus a value that's not numeric at all, which is the infinity symbol. Okay, so greater than 1, we know that we're going to diverge. The ratio test has a wonderful proof that we're not going to include in this lesson. It would probably take a large chunk of our time. It's teachers, it's always something that if you do have time, you can show it to your students. They should be able to follow it. It uses components of the geometric series test quite a bit, and it's usually found in a lot of textbooks, and some components of that proof are actually left as exercises for the students. But you can take that into your consideration if that's something that you want to show your own students. Let's go ahead and take a look at our first example here. For each of the following series, determine if the series converges or diverges. So we're going to use that ratio test, which says we are going to take the limit as n approaches infinity. Remember, it says n approaches infinity of the absolute value of, and then we're going to put the a sub n plus 1 term in the numerator. And it's very important that we do that correctly. It's one of the pitfalls we're going to talk about at the end. But you want to take the n plus 1 term first. So we're going to change all of these n's in this problem to n plus 1s. So we have a 3 to the n plus 1. And then down here in the bottom, n plus 1 minus 1 is going to be an n. All right, so there's my a sub n plus 1 term. Now, I know that the rule, if I go back, says that we're going to divide by a sub n. And we could certainly do that, but to save a little bit of time and to save a little bit of space, let's go ahead and multiply by the reciprocal. That would be perfectly acceptable. I have scored these on the AP exam, and students were allowed to write this as their first step on that free response question. It does convey division. So we're kind of sitting on this for right now. So what we need to do is probably simplify this expression because it's going to be a little tough to take this limit. So let's see what we can do to simplify this. First of all, we notice that this 3 to the n plus 1 divided by the 3 to the n can reduce. We can essentially subtract those exponents because we have like bases, and that would leave us with a 3 to the first power on the top. Now, we've talked a little bit about simplifying various levels of factorial. N minus 1 factorial over n factorial. If you think about this n factorial, he is nothing more than just n multiplied by n minus 1, multiplied by n minus 2, multiplied by n minus 3. Well, for all intents and purposes, basically that n minus 1 multiplied on down is an n minus 1 factorial onto himself. And then at that stage, we can see a cancellation going on between those two guys, and that just leaves us with just plain old n here in the denominator. Okay? And if we go ahead and apply this limit, it's probably pretty easy to see that n is going to get really big, and it's going to cause this particular expression to tend towards 0. And we think about what is the conclusion? Well, this 0 is certainly a value that's less than 1. 1. That's what we want in order to have convergence. I'll just say convergent. When I finish these 3 examples, I'm going to tie this into a graphical approach, and I'm going to show you what the graphs of each of these could look like, and maybe allow us to kind of distinguish convergent behavior from divergent behavior. All right, let's go ahead and move into part B. Same idea. Pretty much, I think that the purpose of showing you a few of these examples is just to kind of alert you to the different algebraic processes that you might have to employ to simplify. So if we're going to go ahead and allow the n to become n plus 1 everywhere, we would end up with something like this. Right? Close out our absolute, close out our fraction here, and then I'm going to multiply this by the reciprocal, right, of a sub n, so that I can get that division happening. So I've got something like this. Okay, now let's see what we can simplify. So we go ahead and begin that process, and we find first of all that the 4 to the n plus 1 over 4 to the n will give us a value of 4, and then likewise the 3 to the n plus 1 over 3 to the n plus 2 would give us a value of 3 to the negative 1, or we could say a 3 that's located in the denominator. Now this n on top and this n plus 1, as much as you might want to simplify, please don't cancel the n's out. We cannot do that. We're just stuck with, we just have an n over n plus 1, and we just have to deal with it. But what's going to happen here is you can think about splitting this limit apart. We're allowed to use that property that says that the limit product is product of the limits here under these conditions, and we don't need the absolute values around 4/3 for sure. And we could talk semantics with this, until we're blue in the face, but when you really get down to it, we don't really need the absolute values around the n over n plus 1, and the reason is pretty plain and simple. N is going to be approaching infinity, and it's starting with a value of 1, so it really never had a chance to be negative. But that really doesn't matter. And the reason it doesn't matter is because, well, the limit of this constant is just the constant, and then of course the limit of this n over n plus 1, if you apply one of the early tricks that you learned in the AV portion of taking limits, is you can compare the exponents of n, and you find that they are the same. They're both 1, so we can divide their coefficients. And so we end up with a limit of 4/3. 4/3 is greater than 1, as you all know, and so that will lead us to determine that this series will diverge. All right, let's go ahead and get one more here just very, very quickly, and that would be this part C. And I'm going to go ahead and take this limit, and we're going to change all of those n's to be n plus 1 at this point. So there we have it. And then dividing by n is the same as multiplying by the reciprocal of 1 over n. So we're looking at this, and then we rewrite our limit statement, and the 4 to the n plus 1 divided by 4 to the n, we do that cancellation, and we would get a 4 up on top. And then if we maybe turn our attention to the factorials for just a moment, we have this n factorial and this n plus 1 factorial. Let me use a different color here, and they're going to reduce a little bit to the point where we are left with an n plus 1 to the first power, very similar to how we reduced in part A. And now you might notice, oh, now I have an n plus 1 to the 10th over an n plus 1 to the first. That will engage in a little bit of simplifying, an n plus 1 to the 9th. And then the only thing that we have left in this denominator is an n to the 10th power at that stage. Right? Now we could separate these two limits if we wanted to. I'm not going to write that down because I'm going to hope that you guys can see, especially right here, if we were to place a limit in front of that expression, we have a degree on top that's less than our degree on bottom. And so this is going to result in another answer of 0 for our limit. It's going to be 4 times 0, which means we are less than 1. So that means that we are going to converge. Yes, we are going to converge at that point. All right. I'm going to go ahead and save this calculator problem for example, for one of our later examples. I think it's going to be a little bit more poignant. All right. So let's take a look at the hierarchy of some of our expressions. So by now you may have noticed that there's a consistent hierarchy of dominance among these single terms. If you have an n raised to some constant, if you have a raised to an nth, if you have n factorial, as long as a and c are these positive constants that are greater than 1, we can sort of apply a pecking order to these, and thus we might be able to make our job a little bit easier to avoid some of this rigorous algebra. So by this, what I'm saying is what really happens as n approaches infinity, right? What value is always going to be the smallest? Which one's always going to be the largest as n approaches infinity of those 3? And I don't know if any of you are big sports fans, but it's, amidst what's going on in our world, we happen to lose March Madness, and last night would have been the NCAA championship game. So I'm kind of sad about that. So we're going to have our own little March Madness. Of course, it's April. So instead of the final 4, we have the final 3. N factorial ends up getting a bye. So what we're going to do is we're going to have n to the c power and a to the n battle each other out in the first round. And this might wake you up, so be prepared. There we go. When n to the c time versus a to the n meet in the ring, a to the n is going to win every time. And what we mean by that is for n's that get large enough, raising a base to an exponential power that's going to change is always going to outweigh an n value raised to a constant. Okay? It might take several n's for that to happen, but as n approaches infinity, we can rest assured that is going to win out. Now, if you remember last week, I actually showed a spreadsheet of that happening in one of our videos. So now we have our championship round between a to the n and n factorial. So they're going to duke it out, and when they do that, it turns out that n factorial turns out to be our winner. By the time n gets large enough, nothing is going to really combat the fact that n factorial is going to be our largest value. So when it all is said and done, cut it out. When it's all said and done, n factorial is going to be our champion. So we can kind of use that idea. If I go back, I'm not going to redo the problem. If I go back to this previous question, say part C, that had a little bit more rigor to the algebra, basically what we could do is say, well, when it comes down to the 4 to the n and the n to the 10th power, this n to the 10th really didn't have a very big role in determining the behavior of that series. So if you were to eliminate him completely and know that the 4 to the n would grow faster, you could apply the ratio test just with what's left, and you get the same result. So it's something that you think about. All right, so let's go ahead and take a look at this. Not so much an example here, but it says, what do each of the following series have in common if we tried to use the ratio test to determine convergence and divergence? I'll let you kind of look at those and think for a moment. And what we see is that this first series, this expression 1 over n plus 3, what do you think he behaves like? If you kind of go back to one of Brian's lessons from last week using comparison tests, doesn't this sort of compare to potentially 1 over n to the first? All right, well, we're going to leave that right there. Let's take a look at the second one. What does this guy compare to? Well, the 2 coefficient in front of the n really doesn't matter much. The -1 matters not at all. And we have this n over n cubed, which would reduce to 1 over n squared. And I think that would be a very favorable thing to compare this to. And if we do the same thing with C, the comparison that we have there is, and I don't want to lose sight of the fact that this is an alternating series, so I'll put that alternating component in. But when I do the comparison, I probably construe 1 over n as being comparable here. So what I'm going to do here is just very, very quickly use the ratio test with just one of these. And I think our solution key that's going to be posted later shows the details of the ratio test for each. So if we just do part C here for just a moment. So if I take the limit and let n get super big on us and take the absolute value of -1 to the n plus 1, and then we'll change my n to n plus 1 in the numerator and do the same thing down here in the denominator. Oh, this will be fun. N plus 1 quantity squared minus quantity n plus 1. And then I could divide that by my a sub n expression, which would be the reciprocal multiplied. So I'm going to put the n squared minus n up here. I'll put my alternating component down here, let's say, followed by my n plus 3. So wow, this is a lot of fun, isn't it? So if we go ahead and we start the process here of simplifying, a lot of things will happen. First of all, -1 to the n plus 1 over -1 to the n would produce a -1 to the first. And I don't really trust myself yet with trying to simplify anything before we may expand out some things here in this denominator. So if I go ahead and expand this n plus 1, I have something like that, and then I'll subtract the quantity n plus 1. All right. And notice I still have an n squared minus n up here, and I believe I still have an n plus 3 to account for in that denominator. So far that's where we're at. And we notice that some things will kind of cancel and reduce here. In fact, I'm just going to go ahead and call this n squared plus n. And then I notice that we could do a little bit more factoring and reducing. And rather than write another step, I'll just reduce that here within this step. And after my factoring, I notice that we can reduce out again. We can cancel away an n. So let's reset and see where we're at here. We have the limit limit as n approaches infinity of the absolute value of -1, and then we have our n plus 4 quantity n minus 1 on top. Remember this n reduced away and cancel. And then in the denominator, if you can see, we have an n plus 1 and an n plus 3 that's left. Now, if we start thinking about, well, what is this limit going to be? Well, if we extract the constant away and the absolute value of that -1 is a positive 1, and therefore the limit of that the limit of that positive 1 is just 1, I'm basically left with the limit of n plus 4 n minus 1 over n plus 1 n plus 3, which if you do your little procedure that deals with finding the degree of the n on top and on bottom, they're both 2, and the coefficients are going to be 1 in front of each, so our limit's going to be 1, which means that I guess we just wasted our time, right? The ratio test is inconclusive. But I wanted to kind of cycle this back, and the reason why the ratio test will be inconclusive is that if you look at each of these series, they all have something in common, and that they could all be classified as a power series, right? Now, the first one's a harmonic, but that's still a power series. The third one is an alternating harmonic, which is still technically by virtue of a power series. So what you want to see here is that the ratio test is always going to be inconclusive if you have a power series, and you can find that out if you wanted to work on your own to verify or at least look at our key. All right, so you're definitely going to want to use some of those earlier tests when you have power series. All right, let's take a look at our example 2 here, and I'm just going to do a few of these problems. Let's take a look at our first one here. Part A says, for each of the following series, find all the values of x for which the series converges. Well, you're still going to use the ratio test, but you can see that we have a little bit of a different situation going on when we truly have a power series. We have x that's still located in our nth term expression, so we'll deal with that accordingly. So we're going to take the limit as n approaches infinity of the absolute value of, and then we have x plus 3 to the n plus 1 power over n plus 1, and then if we multiply that by the reciprocal, that's going to be n on top and x plus 3 to the n on bottom. All right, now we go about our simplification. Now our simplification process involves dividing these x plus 3 expressions, these bases, which means that we can subtract their exponents. So we have an x plus 3 on top, and then this n and n plus 1 in this separate fraction is not going to reduce, so we just have to pretty much leave it as is. So now as you can see, we have an expression in terms of x now. That's the difference between dealing with a power series and using a convergence approach versus just a plain old well-behaved series. So we are going to go ahead and separate these two limits, and it is very important that we realize that the x plus 3 is still in absolute values because we don't know the value of x. It could take on a negative quantity after we had 3, and then we'll do the same thing here in dealing with the limit of n over n plus 1. Now, what is the limit of the absolute value of x plus 3 as n approaches infinity? Well, n can get as high as it wants to be, right? And that's not going to change anything about x plus 3. So we still have x plus 3 located within its absolute values, and then the limit of n over n plus 1 as n gets big is of course going to be 1. Now, what we want to have happen in order to converge, right? If we want this to converge, then the ratio test says that our answer must be less than 1. So we have to solve this inequality to achieve our interval. Now, you can see that if you're centered at -3 and you have a radius of 1, you could probably piece together that inequality very easily. But if you want the practice of solving a nice absolute value inequality, it's not difficult to do here. You would go ahead and set it up like I did, subtract 3 from all sides, and it looks like you'd have something along the lines of this. X would lie in between -4 and -2. However, we're not done yet. What we have to do with this particular problem is check the endpoints, because those are going to be extremely important. So take some space here, and we're going to check, let's say -4, and you will plug -4 into x into the original expression here, into the original series. So you'd have the summation as n goes from 1 to infinity. -4 plus 3 is, of course, -1 to the nth power over n, and hopefully we see that that is a conditionally convergent alternating harmonic series, right? So we know that this is going to converge, albeit conditionally. And then we'll check our -2, and you're probably seeing how this ties back very nicely to the warm-up that we began with this morning. And if we plug in our -2, we add 3, of course, we get 1. 1 to the nth over n is going to be just a normal harmonic series that diverges. So what we have here is a series such that the convergence does occur at -4, but will not occur at the -2, I should say. So it's an open interval there. And these questions do pop up on the AP exam from time to time. Like I said, I had read one of these in my past, and a lot of times they're worth as many as 4 points because there's lots of components to this particular procedure. In the interest of time, I'm going to probably have to forego doing one of my other couple of examples, but I would like to at least take a look at part C here for this example too. So if we take this limit as n approaches infinity, and we take the absolute value, and we replace all of the n's with n plus 1, and then I'm going to multiply by the reciprocal again. All right, hopefully that looks good. We begin our simplification process at this point. -1 to the n plus 1 over -1 to the n will be -1 to the first. And if I simplify my 3x base, this was a little bit trickier, but you have an n subtracting the quantity n minus 1. You can think of it like this if you need to write it off to the side, and hopefully you can see that as a positive 1, right? So that should be the exponent of our 3x all to the first. And of course, n factorial over n plus 1 factorial. It seems like we're seeing those combinations quite a bit is going to reduce to n plus 1. Now, the -1 is for all intents and purposes going to go away because we have absolute values around it. We can then break apart our two pieces and have the absolute value of 3x by himself, and we can take his limit, and then we can multiply that by the limit as n approaches infinity of what's remaining, which is 1 over n plus 1. And what we notice is that if our eyes are drawn to this limit immediately, we see that he produces a 0. And what that means is it really doesn't matter what this limit is. Well, I know what it is. It's the absolute value of 3 times x because there's no n in that expression. But this is going to be a 0 regardless. And we know that 0 is less than 1, of course. Now, that's not an interval, right? That's sort of a statement that says it doesn't matter what x is. This particular series is going to converge everywhere. So you could just simply write converges for all real numbers, or you could use inequality notation with infinity and negative infinity, and that would work well. Okay? Now, I'm not going to solve E to its conclusion, but there ought to be something about this that definitely alerts you to, whoa, wait a minute, does this thing even have a chance of converging? It seems like we're just going to be adding many large numbers, forever. And that's indeed what's going to happen. Now, I still invite you to go ahead and use the ratio test for this. But what would happen is that you should end up getting a value of infinity after you have performed your limits. And we know that that infinity is certainly greater than 1. And so we have to be able to interpret what this really means. And it means that there is no interval of convergence per se. But that doesn't mean that there's no convergent behavior at any particular moment, because we have to realize that no matter how divergent a power series might be, we know that it's at least reliable at where it's centered. And that's going to be a very prominent feature in tomorrow's lesson. So we can see that this guy is centered at 1. So that means that we at least know that we converge at x equal 1. And if you take a really quick look here at the last 3 problems, I have a graph of each one. Now, I had to exercise a little bit of mathematical freedom here, because many pieces of software, Desmos and so forth, will struggle mightily if you try to put infinity up at the top. But if we put something like 100, if I were to add all the first 100 terms, it's going to convey a graph that's going to be very reliable. And so for our first problem, if you recall that converged from -4 to -2, we kind of see that we have some predictable behavior along that interval. But boy, if we move outside of -4 to -2, all bets are off. I mean, if you see this vertical line here that just kind of ascends up into the sky very quickly, we know that something's probably not correct there. And likewise, if we were to kind of look at the upper end of this, we're going to have a very similar behavior. Right? This series might sort of mimic a very common everyday function, but it's only going to do so and do so reliably between -4 and -2. If we look at the second problem, that's the one that, remember, converged everywhere, right? We have a graph that doesn't quite have those very abrupt vertical motions to them that would kind of indicate there's lots of divergence happening. This is a graph that we could rely on, and it's pretty much convergent everywhere. Now, the last one that we did is the most interesting, and here's what he looks like. Lots of crazy divergent behavior there. But here at 1, right, it's almost like this is a really skinny, I don't want to call this a parabola because that's not what it is, but it has those characteristics. There's like this vertex value here that we could rely on as being convergent. So you can kind of see a visual kind of reinforcement of those ideas that we just talked about. All right, the check for understandings here are essentially going to be some problems that we want you guys to do on your own. These are fantastic, always true, sometimes true, never true problems that Brian devised. And so we really encourage you guys to take a look at this. I would like to do just the first part, 1A, for you to kind of give you a taste of what this would look like. So we have this series, and we know that it diverges when x is 4. That's going to be really important. It says determine if the following statements are always true, sometimes true, or never true. And what I find that's really helpful is to draw a number line and place the really key ingredients. That would be the centered value, that would be the value that I know that we might diverge, and then I can start to kind of get some kind of a visual approach to the problem. So here's the -2 that we know that we're centered at, and we also know that we diverge when we get out here to 4. Now the question that we're trying to address is what's happening at 5. Well, if we know that we diverge 4, it could be for a variety of reasons. Maybe the interval of convergence stops well before the 4. It's also possible, we don't want to take this out, but it's also possible that we could take this all the way to the 4, and maybe we have this divergent behavior at that endpoint. Well, no matter what, 5 is going to be outside of that interval. So we can pretty much rest assured that this is always true. So we'll just put the A there. Okay, let's finish up here. I will do B to kind of show you some variation. If we're still centered at -2, and we still know that 4 lives in this divergent zone here, the question that we're addressing is what is happening here at -8. This one's a little bit more interesting. So if we look at this, maybe we could think about what the radius of convergence is. And we can see that the distance between these two values from the center to that outside is 6. Now, am I saying that that's definitely the radius of convergence? It might be. I don't know. But if I were to say that 4 was the far right endpoint, of which it could be, I could have divergent behavior at the end. And if I apply that distance of 6 to here, I see that -8 would be the left end of my interval potentially. And if you recall, the left endpoint of an interval could converge, but it could diverge. So we have a situation that could look like that. We're not saying that it definitely will look like that, but it could. And therefore, we have the idea that sometimes this could be true. Okay, so these are really great problems. And you'll notice that there's a collection of 3 of them in the PDF file. And then it follows up with 3 other problems, practice 4, 5, and 6, that are sort of standalone short answer questions that do foster some really strong conceptual understanding of what's going on. All right, so our debrief and summary here, our enduring understanding. Again, the idea of applying limits that allow us to determine the finite sum of infinitely many terms, but now we also couple that with power series that allow us to represent associate functions on appropriate intervals. When applying the ratio test, our key takeaway is that the limit, now I have it right, as n approaches infinity of that ratio's absolute value is going to be able to determine convergence or divergence. We just check to see if we're less than 1 or if we're greater than 1. And of course, if we're equal to 1, we're going to be inconclusive. And it becomes really important to check those endpoints to determine whether your interval of convergence has convergence at those particular locations. Common misconception, students may sometimes reverse the order of the numerator denominator. I know sometimes my students have done that. They kind of get this confused with maybe the limit comparison test that allows you to have that flexibility. Always make sure that the a to the n plus 1 is in the numerator. And it's also very easy for students to be so focused on finding just the interval of convergence that they forget to check each one. So don't forget to do that. All right, your AP exam practice problem, opening the door to Taylor polynomials, as you can see. So you're going to consider this particular series. It's a 3-part question. You're going to find the summation of that particular series when x is 1 in part A. And part B, you're going to determine if that series is absolutely convergent, conditionally convergent, or divergent. And then in part C, taking the derivative of the individual terms of that series, all right, calling it the series b sub n, and we're going to ask you to find the interval of convergence of b sub n over n squared. So you can either take a photo of that, or you can certainly access it through the PDF file that we have in our Dropbox. All right, we're going to tweet out really quickly here. AP Teachers Rock. We want to definitely give a shout out to Mrs. R. Mrs. R always prepares us for everything in calculus. She makes sure that we learn the material and productively struggle. I love that phrase. I use that all the time with my students. One of the best teachers I've had in high school. So thank you to the students that are recognizing Mrs. R. And for our students that rock, we are incredibly proud of the AP BC students at Legend High School. Perseverance is extraordinary, tough times. Stay strong, stay healthy, keep studying. We love and miss you all. Once again, we want to make sure that every student has access to the technology that could be required to learn from these virtual lessons, and of course to take the AP exam. So if you know somebody that is in need, have them reach out to cb.org/tech, and we'll certainly take them. We'll take care of them. And we want to make sure that you tune in tomorrow. Brian's going to introduce Taylor polynomials, and that will carry over to my lesson on Thursday. And rumor has it that Brian is going to somehow clone his dog buddy. So you definitely want to stick around for that. That's going to be a lot of fun. So until then, we want you all to stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus, Taylor polynomials, infinite series, differential equation, calculus, Taylor polynomials, infinite series, differential equation.
Welcome everybody to another edition of AP Calculus BC Live. My name is Brian Passwater. We're going to be taking a look today at one of the most important topics in all of Calc BC. When you kind of get older and look back at your life, probably like your parents or something like that, they don't remember much about high school usually, but they remember kind of like bits and pieces. So I think a lot of people as they get older, they think back about Algebra 1, and they don't remember much about Algebra 1, but they remember the quadratic formula. They remember singing a song to memorize how to quadratic formula, or they don't remember much about geometry, but they remember doing proofs. In pre-calculus, they remember all the trig that they learned in pre-calculus. Well, one day when you learn, you get older, you kind of get older and move past the classes you're in right now. Most people, when they think back to Calc BC or Calc 2, what they remember is Taylor polynomials. So it's kind of like the big encapsulating idea of Calc BC that makes it unique and makes it important. So there's only 5 topics that the Calc Board is able to include on this year's exam, and they make sure that Taylor polynomials and approximations was one of those 5 topics, because it really is a pivotal important topic that ties a lot of things together of what we've been learning, not just this whole year, but even in previous years as well. So today, we're going to start our study of it, and then Tony's actually going to continue it tomorrow because it is that important and that big of an idea. So we're going to jump right into it so we can get things done. As I mentioned in the intro, my name is Brian Passwater. I'm a Speedway high school teacher in Speedway, Indiana, and the last couple of days I've been sharing a little bit more about myself. That we're getting more comfortable with each other. And I shared the same picture last on Monday when I was presenting. These are my 2 kids when they were younger and our dog Buddy, and I included it again today because I mentioned on Monday, Tony teased it at the end of his lesson yesterday. We're going to attempt to clone my dog Buddy. Who wouldn't want to clone him? Look how adorable he is. Such a cute dog. And so he's not a puppy anymore. He's still pretty adorable. So we're going to clone him here a little bit. So I'm going to continue that picture. But I shared something different about myself. I'm going to try to share something different each time to get a little bit to know a little bit more about me. And so today what I'm going to share is that I have a top 50 list. And what is a top 50 list of, you ask, right? That's what you're wondering. Is it my top 50 movies? No, not my top 50 list of movies. It's not my top 50 list of Netflix shows that I've been binge watching during this quarantine. It's not my top 50 places I want to visit around the world. It's the same top 50 list I'm sure everyone has. It's my top 50 list of all-time favorite mathematicians, right? And so if you have your top 50 list, you might want to get it out today and kind of brush it off and maybe compare notes. But I put a big blue box on it because I don't actually want to reveal much about the list. This is a little screenshot of what was from the list. And that 719 on top is because, like any good top 50 list, I had to revise it every single summer. So in July of 2019, last summer was the last time I updated it. I like to read a lot of biographies and learn about different mathematicians. And each year, as I learn more and kind of discover some new things, I'm able to move some people up the list or down the list or change the list a little bit as I like to go back and check it. So I'm not going to reveal it on here, but I am going to put it on today's Dropbox for you. That way, you go get the materials for today. You're able to see that list, and then you can compare it to your own list. Like I know that you have. And then maybe we can debate a little bit. Maybe we can talk about how we have mutual affection for a certain mathematician, or maybe you think I have somebody that's ranked way too high or way too low on my list. But we can discuss, who you like and who you don't like on my list. So that'll be in the Dropbox. And like we've mentioned in all of these sessions, at the bottom of each video with comments, goes a link. And if you click on that link, it takes you to a Dropbox where it'll say Isaac Newton has shared this with you. Spoiler alert: Isaac Newton takes a prominent role on the top 50 list. I won't say whether he's number 1, number 2, or number 3, or where he's at. But he's definitely in the top 3 because of all of his amazing contributions. One of my favorite people of all time in terms of mathematicians. But if you click on that Dropbox link, you'll be able to get the handouts that we're doing today. Then each evening, our friend Ted types up really detailed solutions for each of these handouts, each of these problems that he puts up there as well. So you can go back and see not just the answers, but the detailed solutions. So thanks to Ted for always doing that. And so copy those, print those off. We always include more problems on our handouts than we could possibly do in a single lesson on here as well. So we've got lots of extra practice problems to get you ready for the AP exams. So some upcoming lessons. Well, this week we're going to finish out our study of Unit 10. This is the last unit in the Copy C material. So today I'm going to be talking about Taylor Approximations Day 1. And then tomorrow Tony's going to come on and do another really amazing lesson on Taylor Approximations Day 2. And then Friday I'll be back to wrap up our discussion and our Unit 10 with alternating series airbound. And this is not a topic that's tested on the exam, but please come on Friday for a couple of reasons. Number one, it doesn't do a lot of good to create these approximations if you have no sense of how good they are, right? I mean, anybody can approximate anything. Someone said, hey, how many windows are there in New York City? I don't know, 100, a billion, 50. Anybody can approximate. But if you don't have any sense of how accurate or how close it is, the approximation doesn't really have a purpose or a meaning. And so one of the ways that we can decide how good our approximation is the alternating series airbound. So we're going to be able to tie this back to our alternating series that we learned earlier, which is tested. But also we're going to be doing more with Taylor approximations. So really, even though it says alternating series airbound, it's almost like day 3 of Taylor approximations. And then following this week, starting next week, you're going to have 3 entire weeks chock full every day, Monday through Friday, right here, 9 a.m. Eastern, of AP Calculus, BC Prep, and Review. And each day I pretty much told you it's going to be life-changing, amazing, the most awesome thing you've ever probably seen. And I've definitely made some empty promises in my life, like Michael Scott said. But hands down, this might be the most generous one. Is just telling you how amazing it's going to be. I hope it doesn't become an empty promise. I really think if you come to these sessions, you're going to be really well prepared for this year's exam. And speaking of this year's exam, I'm sure by now you've heard the exam is modified this year due to the unique circumstances that we're facing. The dates are on there for you. And I only want to highlight one thing on here because Tony and I will keep mentioning and discussing the exam now that the College has released a little bit more information about it. But I want to highlight the idea of the 2 FRQs, right? Typically, an exam will have 45 multiple choice questions. It's about an hour and 45 minutes is how long they would give you to do those problems. And then that's followed by another hour and a half of 6 FRQs, 6 response questions. Well, this year, because it's going to be take home and online, they reduce this to one single 45-minute test. And the first question, FRQ, is 60% of grade. That's 25 minutes in length. And the second question is 40%, which is 15 minutes. Now, what does that mean? Well, I want to point out a couple of things to you. We don't really know exactly what the test is going to look like because it's going to be different. It has to be a little bit different, right? Because of all the unique circumstances. So we're kind of speculating. And to be, full disclosure, Tony and I know nothing more than anybody else out there, right? We have the exact same information that you do. What we have is some experience as college consultants and longtime AP teachers that we can kind of throw on to kind of help us predict what might, appear, what might look on this exam. But again, it's all speculation. But if we're going to have a take-home test, and College Board's already announced that they realize that at your home, you're going to have access to Google, you're going to have access to your books, you're going to have access to your notes, and there's no way to really prevent students from doing that. You're going to have access to apps like Photomap or Wolfram Alpha where you can take a picture of a problem and it gives you a worked out solution. So how can they write a test that can still measure your understanding under these constraints? Well, it turns out that people at College Board, the test development committee that makes the exams, ETS that makes the exams, they're all pretty wicked smart. They're the most intelligent people I've ever met in my life. And so I have no doubt they're going to come up with it's a really good, fair test to really measure what you know. But it also makes me understand, I think, that the questions are going to look a little bit different. That hopefully we're not going to see a lot of questions where you can just type it into a calculator and look up the book. They're going to have to be a little bit more conceptual in nature. So if you've noticed the problems that we're doing in these lessons, especially these AP exam practice problems that are new that we're writing each day, this is sort of how we envision the test might be looking like this year, right? It's going to be a little bit more conceptual, a little bit less just, plug and chug numbers to see whether you understand it, that you can't just look something up on Google. And so take a close look at the kind of problems that we do, especially after we introduce a topic. We start going to those check for understandings, we start going to those AP practice problems. Those are really good indicators of how you might be prepared for this year's exam. And then starting next week, we're going to keep writing new questions. All the questions that we're giving you are brand new. They're the questions that I'm writing to help you get ready for this year's exam and how it might possibly look. And so try those problems each day and see how well you're doing. And starting next week, we'll just keep generating those as we prepare for the AP exam. So at the end of each lesson, we have an AP exam practice problem that we challenge you with, and then we use that same problem as the warm-up. And so this is the problem that I posed or Tony posed at the end of his lesson yesterday. And I've been doing pretty well for Tony's lessons at the end. I write the AP practice problems and kind of work together on them. But I can pose these questions and Tony can tweak them or add to them or kind of give his own changes if he needs to. But I'm giving sort of the ones that he's introducing a little bit easier. The ones that I'm giving a little bit more difficult because then I know that Tony's stuck with the hard ones to try to explain on the air. And I can have some easier ones. Well, I got a little bit mixed up, I think, in my days. So the problem I gave wasn't totally difficult, but it was a little bit challenging, a little bit tricky in places. And so today, I want to spend as much time as possible diving into Taylor polynomials and Taylor approximations. It's a really heavy topic. And I want to make sure that you can't just do examples because remember, the examples that you see in the book are things that you could easily look up on Google or Photomath on the exam. We know we're going to see a little bit more creative questions that doesn't allow you to do that on the test. So I want to make sure we understand the concept behind Taylor polynomials and not just can we mirror or can we mimic a formula and try some problems, right? We have to get to the heart of it. So as much time as possible on that. So because of that, for today's warm-up, I included the typed up solutions that Ted got typed up for us yesterday. This is an example of how it will look. So I'm not going to go in super depth, but I recommend and challenge you to go back and really look at these problems. But if you try them, you can compare your answers. For part A, it does ask us to find this, right? That's a little bit weird to say find something. A lot of times my students are like, what does it even mean? Like, I found it. It's right there. It's sitting on the paper. We forget sometimes that the summation sign, the sigma symbol, is a command. Just like an integration symbol is a command telling you to do something. This is a command telling you to add something up. And sometimes with series, we actually know what it adds up to. Most of our discussion has revolved around just knowing whether it does add up to something or whether it diverges. But then we also learned that unique series that Tony taught us called geometric series, which not only can we figure out if it adds up to something, we can figure out what it adds up to. So it says find something, especially right now in this course, we pretty much know it's going to be asking for a geometric series. And so find the sum when x is 1. So we plug in 1, we get this geometric series, and a is 4 and r is 1/3. So we had a nice formula for that. And the answer, if you worked it out, ended up being 6. So the sum of the series when x is 1 is just going to be 6. And then part B takes us back to our idea of absolute versus conditional convergence. And so now it says, well, what if x is 4? Let's kind of play around with that a little bit. Well, if x is 4, it creates this alternating series. Because it's alternating, it brings up this idea as is it converge first of all? And if it does converge, did it converge because it was alternating, or did it converge despite the fact that it wouldn't have mattered at all, not it would converge no matter what? In this case, it ended up being a geometric series again, where R is 2/3, so we know that it converges. And then because it's geometric, it has to be absolutely convergent. We had this discussion of conditional versus absolute convergence, and Tony hit out again with our ratio test yesterday at the endpoints. Well, a fun little fact: a geometric series can only absolutely converge or diverge. It cannot be conditional. The conditional part can only have other series that aren't geometric strictly in nature. So this is going to be absolutely convergent. And then part C, differentiating the term. So we don't get to dive into in depth the idea of power series this year, whereas power series is another big idea connected really closely to Taylor polynomials and Taylor series. We don't get to dive into that in this year's exam, but they're still important. So Tony and I have been kind of sneaking in power series in the midst of talking about ratio tests and Taylor polynomials. And these are all examples of power series. We're working with them without really thinking much about them as power series. But one of the things we do with power series is we can differentiate them and we can integrate them just like we would a normal function a lot of times. So if we took the derivative and we just gave you the derivative, it creates this new series called B, and we're going to find the interval of convergence of this new series divided by n squared. So this is really tying into the ratio test that Tony talked about yesterday. So if we apply the ratio test, we get this conclusion of this is our limit, and that means our center was 2 and our radius was 3. So we know our open interval is between 1 and or negative 1 and 5. And then because we use the ratio test, we can check the endpoints. When x is -1, the series diverges, it becomes a p series. But when x is 5, it converges using the alternating series test. So this is a nice problem because it really ties in a lot of the things we've been learning about in this unit that's going to be testable, right? The alternating series test, the ratio test, the p series here, 1 over n harmonic series, absolute versus conditional convergence. So it's all right here, geometric series, and one nice problem. I hope that you did well. Keep trying those problems because they're going to give you good ideas of whether or not you're ready for this year's exam or not. So what are we going to do today? Well, we're going to introduce the idea of Taylor polynomials and approximations, which is a very important concept. And then I think even more important than that is going to be we're going to clone the world's cutest dog. That's my dog, Buddy. You might think that your dog is the world's cutest dog, and maybe your dog is, but in my world, Buddy is the world's cutest dog. And then hopefully we're going to be able to see this connection between our application of series that we've been doing, this convergence idea, with what we're talking about today of Taylor polynomials. So in order to do these things today, I hope we can find derivatives because we're going to need to do that from way back from AV. We're going to need to be familiar with polynomials. We're going to be talking about Taylor polynomials, so hopefully we understand what a polynomial is, and then writing equations of tangent lines, which we did way back at the beginning of Calc AV as well. And we're going to see some questions like this where we have a function like sine, and we want to find an approximation of sine of 0.2. Now, obviously, if I want an approximation of sine of 0.2, you could currently just go calculator, and you would just type in sine of 0.2. Well, we're going to find ways to do that before we had access to technology like calculators. So without further ado, jump in. So before we can really talk about Taylor polynomials and Taylor approximations, let's get this idea of cloning for a second, shall we? So here's a what's up, dog, Buddy. And I went online on eBay in my free time, and I found somebody selling a cloning machine. So this is what I bought. Here's a version of this cloning machine. It looks pretty impressive, doesn't it? And you would think maybe it wasn't that legit. You know, it has like random boots and balloons, but the people told me, they promised me that it was legit. It was a legit machine, right? So here's how the cloning machine works. You have to tell this machine what you want to clone, know what you're cloning. You have to tell it what you want to clone, and it's going to do some stuff, and then it's going to kick out a result. And so what we do is give it some heuristics, give it some traits, tell it what we're trying to clone, because it doesn't know what we're cloning. So if I'm trying to clone my dog, I have to feed it some information about my dog, about how I want my dog to look, right? What are some characteristics, what are some traits? Well, when I think about my dog, I think, oh, Buddy is brown, right? That's an important trait. If I'm going to clone my dog, it needs to be brown, doesn't it? And so in the computer, we enter those traits. We tell it what we want it to match up. And so I want to tell the computer that it should be brown, and the computer is going to send that to the machine, and it's going to generate a clone. So let's go ahead and do that. Let's go and tell it brown and see what it comes up with. Well, it's working, I think. Yep. Okay, it's working. So I told it it's brown, and what did the machine kick out? Oh, wow. First of all, that sound did not wake you up this morning. I don't know what will. It spit out a stick. Is that a stick? It is a stick. No, that's not a very good clone from a dog. I guess it is brown, right? I told the machine it's brown. That's all I had to go with. It came up with, I guess, the first thing in mind that was brown. There's probably a lot of things that are brown it could come up with. That's not a very good clone. Maybe we need to tell the machine more information. Brown wasn't very specific. I don't want it to be a stick. Buddy's an animal, right? It's not a stick. So I'm going to tell my machine this time it's brown, but also don't forget it has to also match up the fact that it's an animal. So let's try that and see what the machine comes up with. If I tell it it's brown and an animal. Okay, let's see what comes up with this time. Oh, look at that. It's a teddy bear. Actually, that is pretty cute. I wouldn't be too upset about that. It looks a little bit more like my dog, at least, doesn't it? Like, at least it's somewhat resemblant if you're really far away. Maybe the picture's kind of blurry. I don't know. But still not quite what I'm looking for, right? So I'm starting to get a hang of this machine. I should probably be more specific. So let's not just say that it's brown and that it's an animal. I should probably say it's living, right? It's not a stuffed animal. It's a living animal. So I kick that in the machine and let's see what it comes up with. Oh, that's a Chewbacca. That actually does look a little bit more like my dog, doesn't it? But again, not quite what we're looking for. We're getting closer, right? Each time I get a little bit more information, it starts to look slowly more and more like my dog. I hope. Chewbacca's way too big. He's like 7.5 feet tall or 8 feet tall. And I already know I'm going to get a bunch of tweets and Facebook messages and emails and texts telling me exactly how tall Chewbacca is. So I don't know exactly how tall he is, but I know he's pretty tall in the movies. So I don't want to be that tall. So let's maybe go back and tell our computer, look, it's brown, it's an animal, it's living, but small. It's not nearly as big as Chewbacca. And let's see what our machine comes up with now. Okay, I think our machine's just playing with me at this point. This is an Ewok, in case you don't remember your Star Wars history. I don't know if it's messing with me or it's confused, but notice it created an Ewok, a little brown living animal that's small, and it also gave it a stick. So maybe it combined that first idea with the Ewok. I don't know. But let's be even more specific. How can I get better at this? Each time we're getting a little bit better. I probably should have mentioned it was a dog. Why didn't I mention that at the beginning? Well, probably because this would have been a lot faster presentation, not nearly as fun. But anyway, if I tell it it's a brown animal, living, small, and dog, I come up with that. Hey, at least we're in the right field now, right? It doesn't quite look like my dog, but at least it's a brown, smaller animal that's living, right? So what if I did it one step further? I kept giving more traits. And what if I meant breed of my dog? My dog's a cockapoo, a cocker spaniel, and a poodle. And I include all that information. Now we get something like that. Now we're on the right track. This is actually not a picture of my dog. It is a brown animal, living, small cockapoo, which is nice. But it looks a lot more like my dog than the other things, at least. Just so you know, this is a modern, up-to-date picture of my dog Buddy here, looking like he's tired of my questions. There's something like that when I tell dad jokes a lot of times. He knows. But you know, it's a little bit better, isn't it? This dog on the bottom is probably a little bit better bred in terms of they probably go to bath every day. Buddy probably uses a bath, but he's not getting one every day. But it's a better idea. So this is the idea behind Taylor polynomials. So we can take a similar approach to clone functions. So it was obvious why we want to clone Buddy. He's adorable. Who wouldn't want to have two of those dogs running around, right? Of course we want to clone him. Well, why would we ever want to clone a function? Who looks at a function and says, man, I wish I had two of those. I'm going to print one off and put it on my wall in my room, hang it up on a poster or something, and carry one in my pocket, right? That's kind of weird, isn't it? I'm going to take that function, I'm going to tattoo it on my arm. Who would ever do? Oh yeah, some of us would. That actually would be kind of cool to take a tattoo of the function on your arm. But anything else is kind of different, right? But why would we want a function? We're going to talk about why. But it's the idea of a Taylor polynomial is how we're going to clone functions. So what is a Taylor polynomial, right? It's a pretty important word. But what exactly is it? Well, let's consider the function e to the x. F of x equals e to the x, and I included a nice little graph of e to the x right here on the screen. Well, imagine it's the year 1715. Why the year 1715? Because that's the year that Taylor pictured here in the slide here. That's the year that Taylor published a lot of his results and information about his studies of these polynomials. Now, he wasn't the first one to come up with these ideas, but he was kind of the one that had the most exhaustive research. It took it kind of the furthest, in terms of mathematics. Because its name tied to it now. He gets kind of credit for it. But 1715 was when he published a lot of information. So back then we didn't have cell phones, right? We didn't have iPods back then, believe it or not. We didn't have computers or technology. Even books weren't as common in normal households. And so how would you find e to the 0.1? How would you do that, right? Right now we just type it in our calculator and get some decimals and say, okay, perfect, right? How would you have any concept of how big that was without a calculator? Well, we don't really have even now a simple way to do that. There is no easy way to do that. But what we can do is try to find a way to approximate those values. And that's the idea behind polynomials. What they're going to do is they're going to take ugly functions. I'm going to call e to the x an ugly function, not because I'm going to call it ugly in the fact that it's a little bit more complex, that we can't just plug numbers in, like decimals or other random numbers, and compute it by hand very easily. And we're going to replace them with prettier ones. Well, if e to the x is an ugly function, what is a prettier function? What's a nicer function to work with? Well, it turns out that polynomials are really, really nice. Because polynomials, right? If I think about a polynomial, I'm just going to make up an example here, like 5x squared minus 1/2 x plus 7, right? That's an example of polynomial. A polynomial, you can plug in any number that you want. I could plug 1 into this and work it out because polynomials only require basic arithmetic, meaning you can add, you can subtract, you can multiply, and you can divide. If you can do those 4 things, you can plug numbers in and then compute it. It might take some work, right, doing it by hand, but at least you have a way to do it. So if we could somehow clone or create a new function that looks kind of like this e to the x function, but it's a polynomial, that will allow us to approximate these more ugly functions. So here's some examples of ugly functions that you might see on the left-hand side, things we might be looking at this semester, like e to the x, natural log, sine, cosine, inverse. Those are all ugly functions because if I said plug in 0.1 to any of those, you really would have no idea how to do that without a calculator. Well, on the right-hand column are examples of some nicer, prettier functions. You might not think they look that nice. They look a little more complicated, but they're nicer in the sense of if I was trying to plug 0.1 in, for example, I could do that into any of these and work it out by hand and get an answer, right? Now, I think beyond the pretty and the nicer functions, we also have the prettiest functions, the prettiest of things. And that's going to be this nice picture of my 2 cats. They're feeling a little bit jealous and left out because Buddy was getting all this attention. So yesterday they were laying on my couch and they were snuggling up and saying, hey, take a picture of us. They're pretty photogenic. So this brother and sister showing some brotherly love, right? So how are we going to create a polynomial that approximates a function? Well, essentially, just like we did with Buddy, we're going to clone the function. With Buddy, we found properties of Buddy, right? He was brown, he was an animal. We took different characteristics and we made sure that whatever we created had the same exact characteristics. So we're going to do the same thing with functions. What does it mean to say we're going to clone the traits or the characteristics of a function like e to the x? Well, what we're going to do when we say that is we're going to clone a value, right? A point on a graph would be a trait. And then the other things that are characteristics are the behaviors of the graph. What's the slope of the graph? What's the second derivative, the concavity of the graph? What's the third derivative and the fourth derivative? And the more traits and the more characteristics that we match up, the more that our clone will start to look like the real deal. And so how do we do that? Well, the first step is we're going to pick a random point, c, that's going to be an x value, by the way, where f is the function that we're trying to clone, and p of x is going to be the polynomial that we're creating. And so I want to take a quick side note and show you some notation for a second. When we create a polynomial, we're going to call a piece of n, typically, where n is the degree of the polynomial, right? We could create a first degree, a second degree, a third degree. Remember, the degree is the highest exponent of the polynomial. And we're going to write our polynomial like this: a sub 0 plus a sub 1x plus a sub 2x squared. And we're going to keep going up and up and up until we get to that highest power, that n exponent, the degree of the polynomial. And so we use these letters a sub 0, a sub 1, a sub 2. Typically, when you learn things like quadratics and algebra, we call it like ax squared plus bx plus c. We use letters like a, b, and c. We don't want to use that lettering system because there are some polynomials, we won't see them in the course right now, but you might have 30 terms, right? It goes all the way to x to the 30th. Well, you're going to have letters pretty soon. So it's a little bit easier and simpler just to call them a sub 0, a sub 1, a sub 2. And you can see how it's already connecting to our idea of a series that we learned Convergence this last week and a half, right? So this is going to be our polynomial equation. And so we need to make sure that whenever we create in our function we're approximating, that they have a point in common. That one trait is they have the same point at that value of c. And c is going to be our center. We're going to call it centered at c. And so this example that I have here in the picture, the center is going to be 0. And this is the point, right? When x is 0, that's the point where all the action is going to happen. As we start making our clones and matching up properties and characteristics, it's going to be matching at the center right there. So we have to come up with an equation or a polynomial that goes through that same exact point, right? Well, here's the issue with that. There's infinitely many polynomials that would go through that point, right? If I said take a graph or a polynomial that crosses that same point as the graph, well, our machine could generate all kinds of things. And there's a whole bunch of polynomials to make, and they may not be very good. It might kind of get a stick right back. The result could be a stick, like, okay, I guess it does go to that point, but it really looks nothing at all like what I'm trying to actually clone, right? And so we want to be able to give it more information, we want to be more accurate. So we don't return things like a stick, for example, for our clone polynomial. So what do? Well, we can match more traits. So one other thing that we can match would be their derivatives, right? What if I said don't just have a point in common, but at that center, whatever we create should have the same slope as our function, right? We want to be able to have the same slope right there as well. And then if we do that more and more and more, the more traits that we create that match up, the more that our polynomial is going to look like the true graph. Okay, so let's look at a couple examples. We can take some of this abstractness and put it into some concrete ideas. So we're going to create a first degree polynomial centered at x equals 0 for the function e to the x, and e to the x is the same graph that was given there. So typically when we're writing one of these polynomials, there's 3 really important pieces of information in the problem that we need to know. The first one is the degree. This one is a first degree, meaning the n value is going to be 1. The first degree means the highest power of x is going to be 1. If it was a second degree polynomial, we go all the way up to the x squared term, third degree x to the third, on and on and on. So we need to know what degree it is, how many things we're matching up. Second of all, we have to know what the center is. In this case, the center is 0. And hopefully it makes sense why we pick 0, because when you pick 0, remember, we're trying to match up a point on the original graph and derivatives on the original graph with whatever we're trying to clone, right? And so whatever point you pick, that center, you really should know the value of the original graph. Meaning I can't match up the original graph with my polynomial that we're going to, unless I know the actual point and the slope on the original graph. So it wouldn't make sense to make the center like 0.1, for example, for e, because I don't know what e to the 0.1 is. I don't even know what the point is on the graph. I don't know what that point is. I can't match it up, right? So we have to pick a point that we know, and the problem will tell you what center to use. And then we have to also know what function we're trying to clone, f of x. F of x is what we're trying to match up. So we have all this information, and what helps me is to be organized. And so if I'm trying to make a first degree polynomial at 0, then I know it's going to look something like this: p sub 1 of x. The 1 is, remember, the degree. And going back to our little formula that I wrote up here, p sub 1 of x is going to be a sub 0 plus a sub 1 x, right? This is my first degree. I would stop there because x is the power of 1. And so I'm trying to create a polynomial that looks like this. Well, that your job is figure out what numbers go there. What's a sub 0? What number would go there, and what number would go where a sub 1 is? And you can't just pick random numbers. We have to find the specific numbers so that the points on f and our polynomial are the same, but also their derivatives are the same. Well, here's how we can do that. I'm going to kind of make some more space down here. The first rule is f of c, the point on the graph of f. Remember, f of c is f of 0, because c was 0 at our center. I need the graph at 0 f to be the same answer of the graph of p at the center, right? We're matching things up. This is how we're matching up the characteristics of the traits at the center. Well, we know what f of x is. F of x is e to the x. So f of 0 is just going to be e to the 0. That's what f of x is, which happens to be 1, right? F of 0 is 1. Well, p sub 1 of 0, if I plug 0 into my polynomial here, I'm going to get a sub 0 plus a sub 1 times 0. I'm plugging 0 for x. So they're telling us if you plug in 0 to both equations, you should get the same answer. When I plug in 0 to p sub 1, I get just a sub 0, which means this answer and this answer are supposed to match up, right? That was one of our first requirements, that we have to clone and make sure they match up. And so that tells me that a sub 0 then is 1. Perfect. We already figured out one of our answers. But I also need to figure out a sub 1, don't I? And to figure out a sub 1, we're going to use the fact that we need their derivatives to match up. Well, what is the derivative of f? Well, if f of x is e to the x, the derivative is still e to the x. This is the reason why we choose e to the x for our first example in most textbooks and most Calc courses, because the derivatives are really easy to work with. And so f prime of 0 is going to be e to the 0. I plug 0 in, which is still 1 in this case. And then I to find p prime of x as well. And we're trying to match up their derivatives. And so I took s derivative and plugged in 0. Let's say p's derivative. Well, if p is a sub 0 plus a sub 1 x, the derivative a sub 0 is a number that's just going to go away. And a sub 1 times x, that derivative just becomes a sub 1. It's just a constant in front, right? And so p prime of 0 is just a sub 1. We plug 0 in for x. There is no x, so we just get whatever constant is there. And those two answers have to match up, right? We're cloning these ideas, we're pairing them up, which also means that a sub 1 is also 0. So we now have found enough information to write our polynomial. Our first degree polynomial that would mirror or clone e to the x is going to be 1 plus 1x. This is our first degree Taylor polynomial centered at 0 for e to the x power. Here's a little picture of what it looks like in blue. This is our original function e to the x. And then in red, that's what we just created. That's our polynomial 1 plus x. And notice at the center of 0, they match, right? They touch right there at the same point. And also at center, they have the same slope. So how good of an approximation is this? Well, we know that we make approximations when you're close to that center, right? When you're near the center, the two graphs are pretty close, right? They look a lot like each other. Now, the further out we go, away from that center, generally speaking, our approximation starts to look less and less and less like the true graph, right? So this is kind of like that teddy bear. I matched the brown and I also matched its animal. So that teddy bear looked a little bit more like Buddy, but still not a perfect idea. And so how are we going to get better and better ideas or approximations? Well, we create more and more matches. And so the same type of problem, we could create a second degree polynomial. Well, a second degree polynomial would be a p sub 2, and that would be a sub 0 plus a sub 1x plus a sub 2x squared. And we're going to create a third degree polynomial. The good news is we've already cloned the first two things, right? We already know from our last example that a sub 0 is 1 and a sub 1 is also 1. So we know those two things. So our second degree polynomial is going to look like 1 plus 1x plus something x squared. And maybe you're thinking, oh, it's always going to be 1. It's always going to be 1 in front. It's pretty easy. Well, if only it was that simple, the answers are always 1 for the coefficients. This would be a lot shorter of a lesson, but it's not going to work out that way. So in order to make sure that we create a match for a secondary polynomial, we've already matched the fact that they have the same point. We've matched they have the same derivative at the center. Now, to continue this, we have to make sure that the second derivative at the center of our function matches. We're going to clone that with the second derivative of our polynomial. So we need to take our polynomial here and come up with the second derivative. This is a p, by the way, because you can see that real well. So here, p prime of x, the derivative, is just going to be 1 plus 2a sub 2x, right? And the second derivative for our polynomial that we're trying to create is just going to be 2 times a sub 2. And we know that to make our clone, we have to make sure that the second derivatives of what we're trying to clone and what we're creating pair up. And so f double prime, well, luckily, since we're working with e to the x, f double prime is just e to the x, right? It never changes. So f double prime of 0 is just going to be e to 0, which is still 1. And that needs to match up with p double prime of 0. Well, if I plug in 0 for my p double prime, we're plugging 0 in for x. Well, there is no x, so we just get 2a sub 2. And these two things have to match, right? We're cloning these things, we're pairing them up, and we're making sure they have the same properties, which means that 1 has to be 2 times a sub 2. And then dividing by 2 tells me that a sub 2 is going to be 1/2. So now we found our a sub 2, means our second degree polynomial that we just created would be 1 plus 1x plus 1/2 x squared, like that. And here's an example, here's a picture that shows the three things that we just done. I'm going to slide it up a little bit so you can see it here. And blue, that's our rich e to the x problem. And then in red, this is what we did on the first example, create a first degree linear polynomial. By the way, you recognize those first degree ones. All last semester when you were learning about tangent lines and creating tangent lines, that's what you were doing, right? You were really creating a first degree polynomial approximation. That's what a tangent line is. But now we're extending it. And look how much nicer in green our second degree polynomial looks. Now, again, it still touches that same point. They have the same thing in common. They have the same slope, right? You have two things that match up. But on top of that, at the center, I made sure that our polynomial in green had the same second derivative, the same concavity. So now it starts to look more like our function. It's a little bit better. Close to the center, it's almost indistinguishable from the true polynomial. And as we get further away from the center, it stays closer for a longer period of time, right? And if we kept going, as you can imagine this, we could keep matching up characteristics. And the more things you match up, the more derivatives you match up, the higher degree polynomials that you can create, and the better it looks. And if we did this infinitely long, right? There's infinitely many derivatives we could pair up. It would just be infinitely long polynomial, which is called a power series or a Taylor series. And so this is how all these things are going to tie together. That we kept going, we could create a perfect model that would create a representation for something like e to the x or sine of x or something like that. So I want to jump ahead a little bit. And I know that's almost 9:45, and I want to share something with you because we just saw one quick example, right? That was with e to the x. It shows you how this works. But do we have to go through the whole process over and over again every single time? Or is there kind of a general rule that we can follow? And so what you see in every textbook is this little box that will say this is the definition of a Taylor polynomial, right? Centered at c. Well, the example that we did was centered at 0. It won't always be centered at 0. So it's centered at c. So x equals c as our center. Well, let's see if we can quickly develop this idea behind a general formula, right? And so we're going to use that same process that a polynomial, right? We're trying to create a clone that looks like this. We're trying to create some nth degree polynomial centered at c. So it looks kind of like what we saw before, but instead of every x, it becomes x minus c because we're centered at that value of c. So it's a sub 0 plus a sub 1 x minus c, a sub 2 x minus c squared, on and on and on. Well, if we're going to create a clone like this, here's what we have to do, right? I want you to get lost in all this proof that we're about to look at. We have to come up with values for a sub n, right? In order to create a polynomial, we had to know what those numbers were in front. And every problem is going to have different numbers depending on the equation, the center, and what kind of degree you're creating, right? And so how do we figure out what a sub 0, a sub 1, a sub 2 is? Well, to find it, we remember to create our polynomial, we're matching things up. That our polynomial, whatever the function is we're creating, it may not be e to the x, it could be anything. We need our function and our polynomial to be the same at the center, right? The same point. We also need their derivatives to match up, right? We're giving more and more descriptors. We want their second derivatives to match up, and their third derivatives, and their fourth derivatives, and their on and on, all the way up to the nth derivative. If we keep matching up those things, we keep cloning those properties, then our polynomial will look more and more like the true function that we're trying to kind of replicate, right? And so we do that by creating these ideas, and by doing these, by setting these things equal. That's how we're going to find all of those a values. And so we're going to do that by finding the derivatives, right? We know what p is. So what p's derivative is? If I want to match up, right, f prime to p prime, I have to know p's derivative. Well, p prime of our polynomial, p prime of x, well, here's our p of x. If we took the same derivative, a sub 0 is going to go away. It's just a constant, right? It's gone. A sub 1 times x minus c just becomes a sub 1. It's just a constant in front. We have a degree of 1 here. Then our second term, this derivative, we bring the exponent down in front. It becomes 2a sub 2 times x minus c to the first power. And then the next term, we bring the 3 down in front. It becomes 3 times a sub 3 x minus c squared, right? We subtract 1 to the power. If we use the chain rule, we're multiplying by 1 because the inside x minus c derivative is going to be 1 each time. And we could keep going, right, all the way until we got to the last term. And it would be n times a sub n x minus c to the n minus 1 power, right? That's our first derivative. Now we would keep doing that. We would keep taking derivatives because I need to pair up every single one of those. Well, we're not going to have time to do all that right now. So here's sort of what it's going to look like. And I hope that you can trust me. If I took this term, we're going to find the second derivative. The a sub 1 is going to go away, and then this next term is just going to be 2a sub 2, and then it's going to be the 2 comes in front of the next term. It becomes 3 times 2 a sub 3 x minus c. It kind of keeps going. And we can keep doing that all the way until the nth derivative. And we get to the nth derivative. All we're going to have left at the end is just n times n minus 1 times n minus 2 times n minus 3, all the way down to just 1 and then times a sub n. There won't be any variables left. We took all of the derivatives until we got to a constant, right? Remember, the ultimate goal here is how do we find all of those a values? How do you find a sub 0, a sub 1, a sub 2? Well, the way we find those is by setting these things equal to each other. I need f of c to be p of c, right? That the function we're trying to replicate is going to be the same as the polynomial at the center. So we need f of c to be p of c. Well, we know what p of x is, right? That was our original polynomial. If I plug c into all of these terms for x, right? I plug in c, plug in c, plug in c at the center. All of these terms are going to cancel because c minus c is 0. They're all going to go away, and all we're going to have left of p of x is that first term a sub 0. So it turns out we need to figure out what a sub 0 is. Well, it's always going to be just f of c. Now, we don't know what f is, right? We don't know what the function that we're trying to copy is, but whatever the function is, if I plug in c into that function, that answer will always be a sub 0. And we can continue this process by matching up their derivatives. If I want f prime to equal p prime of c, well, all I have to do is plug in c into that derivative. If I plug in c into the derivative, all those extra terms go away, right? If I plug in c there, they all go away, and all I have left is that first term a sub 1, which means that a sub 1 is f prime of c. And now we have a way to find a sub 1. It's just the derivative of f at c. And if we continue this process, it's going to be a little more complicated because for the second derivative, if I plug in c for all the values of x, we're left with 2 times a sub 2. Remember, I need to know what a sub 2 is. So by dividing both sides by 2, a sub 2, which is that next coefficient, is going to be f double prime of c divided by 2. And if we continue this process, what we're going to learn is all of those a sub n values are going to be found by just taking the nth derivative of our original function and dividing it by n factorial. And this leads us to this general form, which is this. The definition of an nth Taylor polynomial and an nth Maclaurin polynomial is going to be this equation right here, where p sub n is our polynomial we're trying to use to approximate f. Is going to be f of c. Remember, our a sub 0 is just f of c. Then our a sub 1 was f prime of c. And then our a sub 2 is f double prime of c over 2 factorial. And so we keep going. This is sort of our general form. And so how do you create a Taylor polynomial? Well, all you have to do, your job, is you have to find all of these f values. Whatever function you're trying to clone, you have to find the value at the center, the derivative at the center, the next derivative at the center. You keep going and you find values and you plug those values into this equation, and that is our Taylor polynomial. And we also have something called the Maclaurin polynomial, which is a case where when the center is 0, like we saw on our e to the x example, right? Our e to the x example, the center was at 0. So it makes the problem a little bit simpler. The c is 0, f of c is just f of 0, right? I'm plugging in 0 for c, then f prime of 0, and then x minus 0. So it's just going to be, then you keep plugging 0 for all the c's. It's kind of a simpler version of the Taylor polynomial. We call it a Maclaurin polynomial, right? Can't believe it's in the office. There's a lot of beauty in ordinary things. Isn't that kind of the point? When you look at this equation right here, it's really a beautiful thing when you get to know it. At first, right now, this is your first time seeing this, you're probably thinking, what is happening right now? But when you see it, you realize, and we're going to reinforce this tomorrow and again on Friday, how beautiful this is, how powerful this is, right? And so I want to just create or try, one quick example together that we can do here before we wrap up. And I'm going to do this on practice 3 from the check for understanding. And I want to pick this one because it shows where we don't actually even know the function that we're approximating. On our first examples, I told you was e to the x. It's possible we don't even know what the function is we're trying to mirror, but as long as we know properties about it, we can do it, right? So for practice 3, it says a function h. We don't know what h is. There's some random function h. We don't know what the equation is, but we're going to find a third degree Maclaurin polynomial for h. Remember, the importance here are, number 1, it's a third degree, right? That means we're going to go all the way up to the x cubed term. Number 2, it's Maclaurin, which means the center is 0, c is 0, and then the function is h. Well, going back to our Taylor polynomial or formula, the formula for a Taylor polynomial going to be, in this case, actually, I don't have to say p sub n. We know we're doing a third degree. It's going to be p sub 3, right? Our polynomial is going to be at, or in this case, h, right? We're using our function of h. H of 0, we're using the center, plus h prime of 0 times x, plus h double prime of 0, x squared over 2 factorial, plus h triple prime at 0, x cubed over 3 factorial. This is the formula that we show in that box, right? So I like to write out the general formula down first, and then all I have to come up with my answer is you have to find all of these values right here. That's what your job is. So h of 0, well, guess what? I told you h of 0 is 2. That's pretty cool. H prime of 0, I told you that too. It was negative 1. Hey, this isn't so bad after all, is it? Now, the other two, I kind of stopped giving information, didn't I? Well, but I did tell you this nice little formula here that says the nth derivative at 0 is just n squared over 2 factorial. So if I want to find the second derivative at 0, it's going to be 2 squared over 2 factorial. Right? I'm plugging in 2 for n for the second derivative, which is going to give me 4 over 2, which is 2. So h double prime of 0 is 2. That wasn't so bad. And then finally, the third derivative of h at 0, according to our formula, is going to be 3 squared. Now we're plugging in 3 for n over 3 factorial. Well, 3 squared is 9. 3 factorial is 6, which is going to be 3 halves. And now guess what? We have all of the information that we need to create our polynomial, our third degree polynomial for this function h. And remember, in this case, we don't even know what h is. We don't have a picture of it, an equation of it, but we knew enough information about it at the center to create an approximation. And so our approximation is going to be 2. That's what h of 0 was. Minus 1x, right? I plugged in negative 1 or h prime. And then h double prime is 2. So that's going to be 2x squared over 2 factorial for my third term. And then finally, the third derivative is going to be 3 halves x cubed over 3 factorial. It looks a little bit complex and ugly, but guess what? That is a third degree polynomial that will approximate h based on the information that was given. Wow, that was a lot of information, right? So I want to hopefully let you try this and try something before we start finishing up tomorrow. Don't worry, Tony tomorrow's going to come back and really do a lot more examples with us. I did a lot of the front loading of the instruction. That Tony can do a lot more concrete examples, especially some things you might see on the AP exam. That last example that we did, the check for understanding, will be a good example of what could be on the exam this year. So today, look at power series and how they can be used to associate functions on an interval. We did that through the lens of Taylor polynomials. So your AP practice problem is this question right here. It's a fun little problem. It's a little bit challenging, but you have everything that you need to know. And it ties in some older things with some newer things. So give it a go, and then check your answers late tonight, and then make sure tomorrow morning you tune into Tony as he kind of walks us through these answers, right? As Michael Scott would say, would I rather be feared or loved? Easy, both. I want people to be afraid of how much they love me. You might be fearful of Taylor polynomials when you first see them, but I think eventually you're going to come to love them, especially as I put it together tomorrow and Friday to give you a more complete picture of how these things work. But they really are a beautiful, beautiful thing. So as all members of the College Board has tech issues that they can help you sort through, so email or reach out to cb.org/tech if somebody you know has any problems with technology. And then briefly here, quick as we're wrapping up, we've been doing these AP tweet ups and such. We have a couple of shout outs here. Shout out to Mr. Roundtrip for the most epic calculus class the world has ever seen. Chocolate chip cookies for you once I aced this BC exam. And then from a teacher, so proud of my AP BC students persevering through our series units we're on right now, fighting the good fight. Absolutely. So thank you guys so much. As Kelly Ford said, I mentioned this again on Monday. You guys, I'm like really smart now. You don't even know, right? You guys are doing Taylor polynomials. That is incredible. So kudos to you. Great job. Try these problems in the Dropbox. The solutions will be on there tonight. And then tune in tomorrow for Tony's epic lesson that will wrap this up and give you a better understanding, lots and lots and lots of more examples for your AP exam. So thank you guys for watching. Tune in tomorrow for Tony, and we'll see you then. Thanks.
Calculus, Taylor polynomials, infinite series, differential equation, calculus, Taylor polynomials, infinite series.
Greetings once again, teachers and students far and wide, and welcome to AP Calculus BC Live with our second day of finding Taylor polynomial approximations of functions. We especially welcome our live viewers, and we particularly welcome those of you viewing on the West Coast. Wow, 6 a.m. You must really, really love calculus, because I know you're not up this early to see me talk. But we do welcome everyone that's joining us. If you tuned in yesterday, you witnessed Ryan's extraordinary introduction to our ongoing topic by watching his cloning of his beautiful dog Buddy, and he was able to develop the formula for finding a Taylor polynomial. And today we're going to focus more on solving various kinds of problems that use those particular elements of yesterday's lesson. As you can see, I'm not sitting in my back porch. I'm wishful thinking. I wish I was, but here in Indiana, we had a beautiful day yesterday at 80 degrees, and then some tornadoes decided to come through, and now we have a high today of 48. So it's just kind of wishful thinking for some better weather here in the Midwest. So as always, you can find our documents in the description underneath each video, and we always encourage you to work along with us. We can't say this enough. We seem to say this over and over again, but we typically do write. Brian takes the lead in writing the predominant amount of our questions, and we typically will write more questions and post them into the Dropbox than what we plan on doing in our live stream. So that makes for wonderful e-learning experiences for students far and wide, and then eventually solution keys posted, as you guys probably have been aware by now. My name is Tony Records, and I'm an AP Calculus teacher at Avon High School. And I noticed the last couple of days a sort of melancholy has fallen over our home, and it's particularly centered around a special member of my family, and that is my dog Wendy. And I guess my dog has kind of been along by my side almost every single day. In fact, she's just right here below my feet sleeping. And I guess my dog's been hearing a lot of love given to Brian's dog buddy in the last few days. And I was able to do a little dog whispering. And I found out that Wendy just wanted her time. So this is my dog. It's about a 10-year-old picture, and my dog is quite an older dog. She is now 16, which is like 112, right, in dog years. And this picture here was taken not too long, about 30 minutes ago. And my dog is getting through life. She's about 80% blind and has lost most of her hearing, but we love her anyway. And she's always here with me every morning. And there have been times that I'm a little concerned whether or not you can hear her snore, because she can snore a snore. So if you hear a little kind of vibration, kind of monotone in the background, that's probably it. All right. Also, I wanted to spend a little bit of time just kind of talking about some things that maybe kind of give you a little bit more insight into me. This is probably our last day together individually, because next week Brian and I are going to kind of team teach and take care of the review portion of the course. But I want to give you a little bit more insight to who is this guy that's coming into your computers every other day. And I thought the best way to do that is to talk about one of the passions that I have outside of mathematics. I always sought this balance in my life, and that balance kind of focused around doing something that was a little bit more creative, like playing the guitar. It's something I've done my whole life. I played in several bands and cover groups and so forth. But one of the other things that I really truly enjoy is theater. I've been very, very fortunate to be part of an amazing theater organization here in Central Indiana, Civic Theater, and I've done several productions with them. So I just have some pictures of some of the latest productions. Lend Me a Tenor was one of my more recent roles. It was the most physical role that I had. It's kind of hard to believe that this is the same character me as this, but I kind of played a dual role in the particular production. Some of you might be a little bit more familiar with Arsenic and Oblace. Was more of a rooster there. Perhaps you've read as an assignment Pride and Prejudice. Probably guessed there. That's Darcy. That's a longer hair and real lamb chops there on the sides, mutton chops. My students ate that up for about 2 months that I had to wear those out. My most recent production, I think you and Brian got a chance to see this one, was one of my most enjoyable shows called The Foreigner, which is a wonderful story about the senselessness of bigotry and prejudice. And then I was also in a production for a local playwright called Relative to Ransom. So that gives you a little bit of insight. And the reason why I bring this up is that there are things that obviously students are missing out because of the changes that are going on in the world. But I had just looked at my calendar, and in 2 weeks from today, I was scheduled for an audition for the upcoming production of Mamma Mia, which is now put on hold. But I'm hoping that they keep the production and just kind of push it back a little bit, because that would be something that I would certainly love to do. So outside of that, about the only other talent that I have, it's not golf. Trust me, Brian has seen me play golf. I have an encyclopedic knowledge for 80s pop music. In fact, I challenge my students every year to go on the internet and find a song that charted in the top 40 at some point in the Billboard chart in the 1980s, and I can tell them the artist and typically the year that it was released and about the chart position that it peaked at within about 10. In most cases, many cases, I can probably tell them what key it's written in, because I played so many of those songs as a member of several 80s cover bands. So just some interesting odd information about your AP Calculus BC instructor. Upcoming lessons, we got our finding Taylor approximations today. Brian is going to close out our talk about Taylor polynomials tomorrow with the alternating series. Now, it's really more an extension of what we talked about yesterday and today. And they're your 5 first topics, I guess, of the following week that will center around our AP Calculus BC exam and review. Once again, you're probably already aware your AP exam will be Tuesday, May 12th. We want to make sure that we focus on that, mark your calendars, and the test will be made up of 2 free response questions. And I know Brian is hard at work putting together several what we feel to be potential looking AP questions. Of course, we don't have any way of knowing that, but we're going to do our darndest to try to get you prepared in the best way possible. So we're really looking forward to our sessions next week and those 3 response questions that we're going to send your way. Now, this is not a late April Fool's joke. We are going to kind of switch things up here a little bit on our warm-up. So if you do have the PDF that you're following along with, we're going to actually move to the guide practice example 1 first. What we want to do is really warm up properly. That's one thing I've known in 30 years of teaching and 20 years of coaching. It's very important to warm up. I've coached basketball, I've coached track and field. I was a track and field athlete in college, I coached tennis and soccer, and I know that you need to warm up. So if we jumped into that AP practice problem too early, we pull the brain muscle or something, so we got to be very careful. So we'll take a look at this example 1 now. It says find the 3rd degree Taylor polynomial for f of x equals sine of x, centered at x equal pi over 6. Use this polynomial to approximate the sine function. So what we're going to do is we're going to organize this a little bit. Brian went through the process of how we can develop this polynomial, and it focused very much on the function and its derivatives evaluated at where we're centered. So we're going to start, not that we need to write the original function because it's already there in the stem of the problem, but for organizational purposes, I will put it down. And then we're just going to set about to take several derivatives. So f prime of x would equal positive cosine of x. F double prime of x would be negative sine of x. And then at this point, we're starting to think, okay, well, wait a minute, when do we stop taking these derivatives? Well, we read through the problem here carefully, and we see that we're looking for a 3rd degree polynomial. So that's going to indicate to us that the 3rd derivative in this case is going to be a good place to stop, and that would be negative cosine of x there. All right, then I'll organize another column where each of these functions and their derivatives will be evaluated at where we are centered. And in that case, this is a pi over 6. So we think about, well, what's the sine of pi over 6? What's the sine of a 30-degree angle? And that turns out to be 1 over 2, 1/2. And then for our f prime of pi over 6, we're looking at the cosine of a 30-degree angle, right, which would be the square root of 3 over 2. And then by the time you get here, we're just going to really repeat some of the trig calculations that we've done, albeit with a different sign. In this case, negative. And in the case of f triple prime of pi over 6, we'll have negative root 3 over 2. Right? Just one possible way that you can organize this. It's a very common technique that you might see in a lot of textbooks. Now, at this point, it's like going to IKEA, right? It's like buying some furniture. You just have to assemble this polynomial in the way that Brian had indicated yesterday. And it doesn't really matter what you call the polynomial. A lot of times we might use P for polynomial. I've seen capital T used for Taylor polynomial. You can pick whatever you like. We can use the subscript of 3 to indicate that we are taking this out to a 3rd order, 3rd degree. And we work from lowest degree to highest. And then the first term is just this constant 1/2, right? Now, technically, you could argue, well, isn't there some stuff with this? Well, yeah, you could argue the fact that you do have x minus where you're centered, all raised to the 0 power, all divided by 0 factorial, right? Well, the 0 power and the 0 factorial in this situation are just going to result in 1, and thus we don't really need that information there. But it does kind of tend to help understand how this polynomial will build upon itself. When we go to the next term, we have the square root of 3 over 2. Now, this time it's going to be important to introduce the rest of this stuff. We do need the x minus pi over 6 to the 1st power there. And we could put this all over 1 factorial, of course, but that 1 factorial is not going to really change the value of this, so we're going to choose not to write it. And then we keep moving on to the next term, which is going to be minus 1 over 2, right? But now we have a 2 factorial that we're going to introduce into that denominator. Whether you put the factorial there or not doesn't make any difference, because we all know that 2 factorial is 2. And then once again, you have your x minus your c now raised to the 2nd power. And then one more term, we finish up with the minus square root of 3 over 2. That 2 is going to have to be joined by a 3 factorial, or you could call it 6, or you could multiply it out and get 12 for this denominator, and finish it up with the x minus c all raised to 3rd power. And there you've got your 3rd Taylor polynomial. Now, this particular question wants us to go on a little bit further and actually approximate the sine of 2. And the way that you could do this, if you wanted to show really crystal clear, perfect notation, you want to be careful. You don't ever want to say that the sine sign of point 2 is equal to the Taylor polynomial of third order at point 2. We don't want to put an equal sign in between these, right? We could put an approximately, and that would be safe. And then we could say that this third degree Taylor polynomial is, well, we'll have to go to some kind of technology. And I've actually already typed it in for you. I've done it actually in Zoom or Desmos, which might be a little bit familiar to more of you. It's a free online piece of software that you can certainly use. But there's our Taylor polynomial that we just computed, and I actually have the graph here sketched, I believe. And I can probably move this over for you to see a little bit more of that polynomial. And then I've gone ahead and evaluated a p of 0.2. Desmos does a good job of that. And you can see we get 0.1984. And I took the liberty of actually figuring out what the sign of 0.2 was, its exact value, or its exact value rounded to this many digits at least. And you can see that there's quite a bit of similarity. In fact, we don't start to disagree or, dare I say, diverge until we get to that fourth decimal place. So that would be about 2/10,000ths of a precision. And that's going to bring up a very interesting point in what Brian can talk about tomorrow about, well, how good is this approximation? Now, he might focus a little bit more on alternating series, and this isn't an alternating series, but there are many other, well, one other particular way that you can focus on an error analysis when you don't have an alternating series, and you can touch upon that a little bit as well. And if you're curious, there's what the graph of sign looks like. And we can see that our polynomial coincides to an extent with that sign graph. And if we also take a look at another way to maybe describe this situation, is that we've got our function f of x equals sine of x, and I've developed a Taylor polynomial through the TI Inspire. It's just using a function that's innate to the TI Inspire. And you can see that I've got this slider set up that will tell me what degree of the polynomial I'm going to take. And right now, I'm probably at the worst possible degree we can. I've got a 0 degree, which is a constant, which would be, if you look at your sheet, that's going to be that very first term, 1/2. So my polynomial is p0 equal 1/2, and that's that horizontal line. But as you can see, as I increase that power, I start to see a brown colored graph here that starts to adhere much more closely to this sine curve. And you can see that the interval of convergence sort of grows for this polynomial. And I can take this up as far as I want, well, as far as I've allowed it to. I think maybe I have it going up to about 15, and it's still looking pretty good in the screen that we see. All right, so again, if you didn't get a chance, that polynomial approximation was 0.198 if we decide to round it to 3 decimal places. All right, let's go ahead and take a look at example 2, if you would. And there again is Wendy. This is from a few days ago, sending a message that April distance does bring me existence, and my daughter drew on a driveway. And in this problem, we're going to find a second degree Maclaurin polynomial for the function g of x equals e to the 3x power. And we're going to set this up very similarly. What I'd like you to do is I'm going to give you maybe about 30 seconds, and I'd like you guys to go ahead and list the desired functions g and its derivatives in a column for me, and let's check if we agree. Okay, let's take a look at your work here. So one of the pitfalls, sometimes just performing some of these seemingly simple derivatives can get us into trouble a little bit. So I'm going to start again by just rewriting the g of x just to organize. And did you notice that as you took these derivatives, you had to use the chain rule? So the derivative of e to the 3x would be e to the 3x times 3. We take another derivative, g double prime, and we would get 3e to the 3x times 3 again, but those two 3's could multiply to make 9. You can always check your inventory and make sure that you've taken as many derivatives as you need, and it says that this is a second degree Maclaurin that we're about to find. And the fact that it says Maclaurin is important because you know that means that we're centered around 0, so I'm going to circle that information. So we're at a point now where we can just plug in 0 to each of these particular expressions. So we have g of 0, which is e to the 0, which we know to be 1, and g prime of 0 would be 3e to the 0, which is 3, and then of course g double prime of 0 is going to be 9. All right, now we just assemble our furniture and we write our Maclaurin polynomial. You can still call it a p, it would be of order 2, and we start with our constant 1, that's the g of 0, and then to that we add 3 times what could be x minus 0, but we'll just call that x to the first power all over 1. And then for our last term here, 9 would have to be divided by 2. And I'm going to go ahead and put that factorial there just to emphasize the fact that we are now starting to increase that denominator by an integral amount of 1 factorial, and then we have our x squared, and that should take care of that particular problem. There's really nothing else that we have to do. We're not approximating a certain value of e, although we could use this if we wanted to do that. If we want to take a look one more time at some technology for this particular problem, there's our function e to the 3x in blue, and I again have set up a template where I can compute a Taylor of that function f1 of x, where x is my independent variable. I'm going to take my order to be in, that allows me to let the order be whatever I want it to be, and that 0 is, you can probably guess, is where we're centered. So you can see how if I increase the n, if I take it up to 2, which is exactly what this problem called for, we have some nice looking convergence maybe in this area here. In other words, that polynomial might be pretty reliable to approximate a value on the function e to the 3x. Outside of that, I don't think I would rely on that a whole lot, but watch the graph, particularly the red graph, as I increase the order. Well, first of all, you kind of see it moving up and down, right? It's just going from an even power to an odd power, of course. But you can start to see how we move or meander along the left side of that curve just a little bit more and become more convergent in that negative direction if I take it up to equal 20. All right, I think we're pretty warm. What do you think? I think we can go back to yesterday's warm-up problem, which is our AP practice question. Wonderfully written question by Brian. It uses a lot of elements of calculus. That's not BC, but AB as well. So we're going to go ahead and read this just very quickly. We have a function f that has derivatives of all orders for all values of x, and a portion of the graph of f is shown. And we have the tangent line to the graph of f at x equal 2. We're going to take g and let it be a function defined by g of x equal 3 plus the integral from 2 to x of f of t dt. In part A, you were asked to find the second degree Taylor polynomial for g of x centered at 2. Part B asks, does g of x have a local minimum, local maximum, or neither at x equal 2? Give a reason for your answer. And part C says to consider the geometric series the summation of a sub n as n goes from 1 to infinity, where a sub 1 is g prime of 2, and a sub 2 is defined to be p sub 2 prime of x minus 1. Now it's possible, depending on when you downloaded this, we had to make a little correction to this. So this is now the correct version. So it's possible that maybe you were struggling with part C if you were working on this a little bit earlier. But this is the way that we want the problem to read, and we'll go ahead and make sure we solve C together. And then part C does say that we want to find that summation of a sub n when x is 13.6. So let's go ahead and dive into this for part A. Find the second degree Taylor polynomial. Well, one of the things that both Brian and I want you to make sure that you're aware of is just because you're presented information that's a little bit different, you don't want to make sure that change the way that you go about solving a problem. I tell my students all the time, don't let calculus stand in the way of you understanding calculus. Sometimes that throws them for a loop and they think that I messed up. But just because calculus is presented in this problem in a different way doesn't really change our strategy. And by that I mean, if we want a second degree Taylor poly for g of x, we're going to figure out, well, what is g of x equal to? And then we're going to figure out what's g prime of x equal to. And then we're going to figure out what g double prime of x is equal to, right? Because we know that we want that second degree polynomial. Well, the g of x, again, it might seem a little superfluous. I'm just going to write it down for organizational sake, but it's the expression that function defined as an integral expression that was given to us in the stem. And now when we find g prime of x, what a wonderfully written problem this is. You're going to use something from your AP portion of your course, where you're going to take the derivative of 3 plus this interval. And of course, the derivative of 3 is 0. Now you're using one of the forms of the fundamental theorem of calculus here, where you can just replace this dummy variable t with this upper boundary of x. And we don't have to enforce the chain rule because that upper boundary is simply at x. And then when we go down here to g double prime, we're going to end up taking the derivative of f, which we know to be f prime of x. And I'll tell you what I'm going to do. I'm going to rewrite this f of x just a little over here to the left so we don't fuse that lower boundary as maybe being a square around it. That's never happened to me. So anyhow, we're going to go ahead and plug in the 2 for the x. So when we solve this, g of 2, we're going to replace the x with 2, right? We're not going to let this calculus stand in the way of information that we know. We know to evaluate this function whenever x is showing up, we're going to replace it with a 2. So we know that the integration that has a lower boundary and an upper boundary that are the same, that's going to be 0. And then we just end up with 3 here, right? So you can see that you're going about finding these components of those coefficients for your polynomial in a little bit of a different way. Maybe this is a way that might be more akin to the exam that you're going to see this year, because there is no photo math that's typically going to help you find these coefficients. You have to have the conceptual knowledge of knowing how to put them together. So what is g prime of 2? Well, I'll tell you what g prime of 2 is. It's f of 2. So we have to think about, well, where would we go to find an f of 2 value? And what better place than a graph of f? That's what this particular function is graphing. Function f and all of its derivatives, the portion of graph of f is shown. And we see that f of 2 is going to have this y value that's equal to 1. And then finally, g double prime, also known as f single prime, evaluated at 2, is going to cause us to look a little bit deeper into this tangent line. And we have to have that conceptual understanding that says, okay, well, that means that we want to figure out what is the derivative of this graph at that point. And that just means it's the slope of the tangent line of that particular tangent line. So we have the 0.21 here. We might have to look at this a little bit and maybe trust our eyes. It's a very well done graph, so it won't take a whole lot to see that you're just going to go up 3 units and over 1 unit. There is no scale change. And that's going to serve as that particular f prime of 2 value. So there you have it. You have all of the components. You can assemble your furniture at this point. And we see that we have p of 2, or p sub 2, I should say, the second degree polynomial. We'll start with our 3, our constant. To that, we will add 1 over 1 factorial. We take another quick look at this, and we see that this is centered at x equal 2. So we need to put x minus 2. There's no need to get rid of that 1 there. I know we don't need it, but we can leave it there if we like. And then we can add our final term, which is 3 over 2, or 2 factorial if you want, times the quantity x minus 2 squared. And there is your second degree Taylor polynomial. Now, Brian made a good point yesterday about how a lot of times students tend to get a little scared about Taylor polynomials, even moving into Taylor series in a normal year. And it turns out that these really aren't that difficult. And I think they're one of the most enjoyable parts of the course because they answer a lot of previous questions about, well, how does the, back in the day, how we compute some of these more difficult sine of 0.2 e to the second power type of things without, using the calculator. And this is exactly how our founding fathers did that. But it also kind of opens the door to answer a whole bunch of new questions about how you can integrate really super complex functions. Well, it turns out that we can rewrite them as Taylor series and then go about our integration techniques that we learned. So it's a wonderful ending, I think, to your journey through your high school calculus. We take a look at part B. Part B asks, does g of x have a local minimum, local max, or neither at x equal 2? Give a reason for your answer. Again, let's not let calculus stand in the way of the calculus that we know. It's likely that you are pretty adept at figuring out how to find local extrema. If the function here is g of x, we need to figure out what g's derivative is. So we're going to take the derivative of g. I know there's no traditional looking function called g. It's more of a non-traditional type of function, let's call it. But again, we've already done this. We figured out in part A that g prime of x is f of x. So now what we have to do is figure out, okay, well, what's going on here too? Well, I want to say that we already figured that out as well. We have figured out that f of 2 is equal to this 1. And so we have to rely on the fact that we can only have a relative extrema when your first derivative is either equal to 0 or possibly undefined. And because 1 is neither 0 nor undefined, we can say that g of x has neither. The word local and the word relative are interchangeable terms that you can use on the AP exam. So we'll say it has neither a local min nor a local max at x equal 2. And that's going to give you enough insight. They're going to be able to look over here and see that you had justified that by saying that your derivative is equal to 1. But if you want to kind of polish this up a little bit, you could just simply say because g prime of 2 is not equal to 0 nor undefined. Okay, let's move on to our wonderful part C. It's probably my favorite part of the question. It says consider the geometric series, the summation of a sub n, where a1 is g prime of 2 and a sub 2 is p sub 2 prime of x minus 1. We are asked to find the summation of the a sub n expression when x is 13/6. So the first thing that we want to look at this is kind of understand, what is this question saying? It's saying find a summation. That means you're going to add up a bunch of infinite things. Well, wait a minute, we can't do that unless we have what kind of a series? Geometric, which, okay, that's making sense. So we're going to have to rely back on our geometric series knowledge in this particular problem. Now, geometric series are typically very easy to add, but you have to know a first term, which it looks like we're kind of in the door there, but you also have to know the value of r. If you remember, the typical form looks something like this. You have a term and then r to a power, and then this can kind of serve as your basis of building that formula. Well, the r value in this problem is just going to take a little bit of thinking. We have to really have that conceptual understanding of what is the r really saying? Well, it's what you would multiply a1 by to get to a2. So if you wanted to solve that for r, right, if a1 times r is a2, basically, right, then solving for r is nothing more than just dividing by a1. So there's what you've got. Okay, well, what does this mean specific to this problem? Well, the a2 happens to be p sub 2 prime of x. P sub 2 prime of x. Well, what's p sub 2 prime of x? Well, if you go back to part A, I think you're looking at a p sub 2 right there. And I'm not going to flip back to it. Perhaps you have it on your page, but if we take that derivative, we should end up getting 1 plus, and then we would have, let's see, maybe I should go back and look at it just to make sure, because you might be just following along here. But what we would see is the 2 and the 2 factorial here would cancel, and we would have 3 quantity x minus 2 to the first. So 3 quantity x minus 2 to the first. There is no chain rule that we have to worry about because the derivative of x minus 2 is 1, of course. And then please don't forget there is a minus 1 here, kind of sitting here at the end of that a2 expression. And then we would divide all of that by a1. Well, a1 is g prime of 2. And I want to say for the third time in this problem, we're going to use the fact that g prime is the same as f. And if we evaluate it 2, we're looking at that 1 again. So the denominator is just simply a 1. Well, now we would like to evaluate this very specifically when x is 13/6. So what do we get when we do that? Well, these ones on top cancel. We have 3 quantity 13/6 minus 2, which is really 13/6 minus 12/6, or 1/6, and 3 times 1 over 6 would give us 1/2. Right? So a little bit of work, but that was our r value that we needed. It pretty much that does the bulk of the work for us, because now for the summation of that a sub n expression, all we need to do now is just to realize that we take the first term, right? Well, let's go ahead and compute what that first term is going to be. And that first term is, that first term is 1 in this case, right? We're getting 1, and then we take 1 minus r 1/2, and once we simplify that, 1 over 1/2 is going to be 2. All right, so that takes care of our part C. All right, now we're kind of a little bit off kilter here, so I'm going to go ahead and give you this lesson overview. Now that we're about halfway through the lesson or more, but we're just continuing to investigate the importance of Taylor polynomials. That's what we're doing. They play a very vital role, not just in the world of calculus, but in the world of mathematics as a whole. And we're certainly going to be solving very unique conceptual-based problems with these Taylor polynomials. Well, you should know, obviously, how to develop a Taylor polynomial from a given function. We've done that 3 times already. The difference between a Taylor and a Maclaurin is very important. One's centered at 0, the other's not. And the components that make the coefficients of the terms in the Taylor polynomial seem to be a little troublesome sometimes for students, remembering those factorial values each time. And there you can see another potential question that you could answer given a 4th degree Taylor polynomial with this elusive k here. They can ask you to find the value of k given some information. So let's do this. Let's go ahead and continue a bit with our guide practice. And we could certainly have us take a look at example 3 here. It's a problem that's got a little bit different modality. You're looking at problems or information given from a table. So what I would like to do is I'm going to start the timer, and I'm going to have you kind of read through this on your own and see if you can start to generate those important function values and maybe even get as far as evaluating them at where we need to evaluate them. So I'll give you about a minute to think about this while we play Kareem's wonderful music. Kind of like being on Jeopardy, isn't it? Just with different themes. Now, as you read through this problem, hopefully you came to the realization that there really is no function g of x that you're going to end up taking derivatives of per se. You're going to actually start diving right into those specific functions evaluated at 3, if that makes any sense. So if we need a third degree Taylor polynomial and we are centered at x equal 3, then as I said, we could just jump right in and say, okay, well, what is g of 3, right? We don't have that blue column that I used before, g of x, g prime of x, g double prime. So we look at this and we think, oh my goodness gracious, how are we going to find g of 3? That looks absolutely possible. Well, that's what the chart is for, right? We see our g of x, we see our x value 3, and we can deduce very quickly that g of 3 is going to be 4. Now we go to g prime, and we're starting to really get very fond of this chart because we see a g prime of x is -5. And then we know that we have to take a couple more derivatives, so g double prime comes next, and then, sadness breaks out because we can't use the chart anymore. But if we read very carefully, it does say that once n is equal to 2 or larger, and that is where we are now, then the nth derivative of g, it's x equal 3, is given by this expression. So we could just take that 2, which is our n, plug it in here, so we have f of 2 minus 2, which is f of 0, the 0th degree derivative, which is just the original function f, right, evaluated at 3, and then lo and behold, we're back to the chart. One more time, for g triple prime of 3, if we allow this n in this expression here to be a 3, now we have f's first derivative evaluated at 3, and it turns out that we can use the chart there as well. And we do have this decoy value, this f double prime never got used, but it's nice that it's in the chart to sort of keep us on our toes. So if we write our Taylor polynomial, so p sub 3, I believe is what we want, x, we assemble it 4, then we subtract 5, divided by 1 factorial. Don't need to write that, and we know that we're centered at 3, so we're going to go x minus 3 to the first, and then we just proceed from there. 1 over 2 factorial times x minus 3 squared, and lastly, minus 2 over 3 factorial x minus 3 cubed. And again, it's your prerogative. If you want to reduce these, you can. Just if you reduce them, make sure that you reduce them correctly. But there's nothing wrong with leaving that as 2 over 3 factorial or even 2 over 6. Okay. Several wonderful problems here. Example 4 here in the guided practice is going to be something that we are going to assign for homework, but it has a lot of similar characteristics to the problem that we just did. And if you couple this with example 5, which is another wonderful table question, it again has some similar characteristics. And so you could use your knowledge that you gained from doing example 3 to help there a little bit. I would like to turn our attention now to the check for understanding problems and look. Let's look specifically at number 2 here. Number 1 is a very well written problem as well. They all are. But I'd like you to kind of do some struggle with number 1 a bit because it's got some kind of elements to it. The value k, which kind of is not the most common expression that you might see for a function, but that sort of is the overriding theme. You've got this graph of k and a tangent line. Does that sound familiar? Well, we did see a problem that was a little bit like that at the very beginning of the lesson today, and maybe you can kind of bridge those together. But I really enjoy this practice number 2 that I'd like to work through with you. And it says that we've got the functions f, f prime, and f double prime. They're all continuous. They're all differentiable. And the nth derivative of f is given by yet another expression here. Nth derivative of 1 is the summation as I goes from 0 to infinity of 12 times the quantity n minus 1 over 5 to the I power. And so if you can't read these real well, make sure that you understand these are the letter I. It's the index in this problem. And that particular function's derivative equation is only good for a certain time when n is between 0 and 5. We're asked to find the third degree Taylor polynomial for f of x, and we're centered around 1. So again, the key components here, we have a third degree Taylor. We are centered around x equal 1. We once again find ourselves in that same boat. We don't really need to list f of x and f prime of x and f double prime of x because we don't really know what they're going to be generally, but we do know what they're going to be very specifically. And if we start with f of 1, when we start with f of 1, well, what does that really mean? Well, f of 1 means that we can actually go into this formula and we can replace the n with a 1. So upon doing that, we have a summation expression as such. N is 1, so 1 minus 1, of course, is 0. Well, by the time you take 0 and divide it by 5, you get 0. And if you take 0 and raise it to any power, you're still going to get 0 there. And we're at a situation here where we're going to get 0 as this first particular value. Actually, yes, we're adding 0 several times. Now, if we go to f prime of 1, that means we're going to replace this n with a, and actually, I need to back up, you guys. This is what happens when you get kind of old. F of 1, what is the derivative of f of 1? I actually jumped the gun and I was doing f prime. I was seeing if you guys were paying attention. Let's redo this. F of 1, this is really the 0th derivative. I'm going to plug a 0 in for the n. Let's try that. So what I should have here for f of 1 is I going from 0 to infinity, 0 to infinity. And I should have 12 times negative 1/5 times I. That's what I want there. And it's unfortunate because this is going to be a little harder to add, unfortunately. But we are able to do it because this is a geometric series. So we can see that the first term, if we let I be 0, is going to be 12. And hopefully we all realize that the radius, or the ratio, I should say, the ratio is negative 1/5. So 1 minus the ratio is going to be 1 plus 1/5, which we know to be 6/5. And then if we multiply by the reciprocal of that, I believe we get 10. So f of 1 is 10. Now let's do f prime of 1. If we do f prime of 1, we can then state that the n is 1, and that's where our 0 comes from. And this one is a whole heck of a lot easier to add because you're just adding 0 plus 0 plus 0 many times over. Okay, how far do we have to go? We have to go up to a third degree. So f double prime of 1, remember we're centered at 1 here, is going to allow us to let the n be a 2. So the summation is going to look a little something like this now. We have 12 in front. 2 minus 1 is positive 1, so we have 1/5 to the I. And now you have another series that still is a geometric series that you still can use the formula for. And you always have to keep careful sight of the fact that that ratio, that r, has to be less than 1, has to be strictly less than 1. So our first term is still going to be the 12, and we take 1 minus 1/5. It's like we have 12 over, what would that be? 12 over 4/5. And if we multiply by that reciprocal, I believe we're going to get 15. Okay, boy, I'm glad we only have to do one more of these. F triple prime of 1 is again pretty much going to result in a similar situation where now this n is a 3, 3 minus 1 is 2, we have 2/5 to the I. And again, as long as this r value is less than 1, we are free to use our first term divided by 1 minus the ratio each and every time. And it turns out that this time we get 12 over 3/5, which I believe is 20. Now, if I go back to this, do you kind of understand why this restriction is in place? It's really important because if we were to expand that restriction and say let n go up to like maybe even 6 and 7, we could have an issue with trying to add this, right? We're trying to add an infinite series here, and that could be a little bit problematic for our n value. But if n is 5, we're still safe. But by the time n is 6, we're going to have a 5 over 5 here, which is equal to 1, which loses our possibility of convergence. All right, we still have to write the polynomial, but that's pretty academic at this point, and it's very likely that you're becoming quite good at it at this point. So we have p sub 3 of x is equal to our 10. Now this is kind of interesting, and I wanted to make sure that we finish this problem. You have this sort of missing term, right? This first degree term, the first power term is going to be gone. So we want to skip over him and make sure that you pick up where you left off, and you use a 2 factorial for the denominator of this 15. And of course, the x minus 1 would have to be squared there, okay? And then we write up our last term, and we have to remember that we need a 3 factorial for his denominator, and we have x minus 1 raised to the third. Okay? Again, Brian, I always talk about how there's just so many neat problems here. We just want to work with them and share them with you, but we do find that we run out of time. Sometimes teaching Calc PC in a 45, 50, 55-minute time window is always a challenge. And if you're a teacher out there that teaches PC, I think we're preaching to the choir there. But practice number 3 here is a wonderful 2-part question that throws in this odd, even, piecewise function. That's going to throw just another twist on the way that you're going to figure out some of these coefficient values. And then we have this wonderful problem 4. These are among my favorite questions. I use a lot of these kinds of problems with my own students where they have to extract a certain value within a given Taylor polynomial to figure out what the true derivative value, in this case f triple prime, is going to be. So you certainly want to take a look at this one. It really doesn't take a lot of time to solve, but it can be very tricky. So check this answer. And then I love this one. The last problem. Consider this function g of x to be e to the negative 2x over 3 and find the coefficient of the x to the 26th term. I advise you to not take 26 derivatives. There is a better way, and I'm sure that you probably find that way if you kind of spend a little bit of time. So it's a wonderful question as well. So in this summary, our enduring understanding doesn't really change. Power series will allow us to represent an associated function on an appropriate interval. And our takeaways, just like yesterday, Taylor polynomials allow us to approximate values of more complicated functions. In many cases, cases, we've seen as the degree of the Taylor polynomial gets larger, the polynomial tends to be a little bit more reliable, and it will approach the original function over a growing interval. And Taylor polynomials can always be extended to Taylor series. That leads to the idea of the power series, which although is not a testable component on this year's AP exam, it's always something that you can revisit. And, if you hadn't had a chance to learn that in your own physical classroom or virtual classroom, it's something that maybe you can visit after the AP exam. Common pitfalls: sometimes students forget that the coefficients of the terms of the Taylor polynomial are of the form the nth derivative evaluated at where you're centered over the n factorial. So you mustn't forget that there's that n factorial component that makes that coefficient. And Taylor polynomials can always produce approximations, but we haven't learned how good these approximations are for a desired function yet. But you're honestly about 23 hours away from that if you're going to watch live, because Brian's going to do a great job of kind of putting that component together. AP practice. So your other little homework assignment tonight is just a small 3-part question here where you have a function, all derivatives and orders for real values of x. We're going to tell you that the second Taylor polynomial, the second Maclaurin polynomial for f is going to be defined as p2 of x, and we're going to tell you that f of 0 is 1, f prime of 0 is 0. If p sub 2 of 1 is a half, we want you to find that second derivative evaluated at 0. Kind of ties into understanding how to build those coefficients. Part B is going to ask you to find p sub 2 prime of 0 and p sub 2 double prime of 0, and then we circle back to some AB knowledge. Does p sub 2 of x have a relative min max or neither? X equals 0. Explain. And then finally, we want to use the p sub 2 of x that we had before to approximate f of 1/2. Our tweet outs are still coming in fast and furiously, so we want to recognize the AP Teachers Rock tweet of the day. And this comes from a group of students that say thank you to my AP calculus teachers, Mrs. Pyle and Mrs. and I'm sorry I will butcher that, but maybe Zayek, for showing me the wonders of calculus, which I now love, caring about their students, being great teachers. You can't ask for anything else than that. And Mrs. Again, I'm sorry if I mispronounced that name. And as far as our AP Students Rock, well, I'm a little biased on this one, but this comes from a really good friend of Brian and I's. My AP students are working so hard during our e-learning. I am so proud of them. And this comes from a teacher extraordinaire from West Florence High School in South Carolina, Vicky Carter. Vicky, thanks for all that you've done for the AP community and for Brian and I. We really appreciate it. Again, we always want to make sure that you're aware if you or your friends are having some trouble accessing equipment that they can use for these e-learning lessons, or by the time they take their AP exams in all subjects, or if internet is a problem, please have them reach out to the College Board at cd.org/tech, and they'll certainly do their best to take care of all the issues that you might not be having there. They're really wanting to work with you on that. And we want to thank you for watching. We hope you'll join us again tomorrow. Brian is going to be in to wrap up our last lesson that's kind of teaching the new content, but he's going to really put a nice finale to our study of Taylor polynomials. And we're going to take you out with our outro music by our good friend from New York. We want to thank Anthony G for this wonderful outro music. And until then, I want you to stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus. Taylor polynomials. Infinite series. Differential equation. Calculus. Taylor polynomials. Infinite series.
Well, good morning, everybody. When you hear that music, it's time for some AP Calculus BC live sessions here on College Board's YouTube channel. Today, we're going to be looking at our last topic in Unit 10, alternating series airbound. And I don't want to cause any confusion. We are going to be looking at the alternating series airbound, but really, we're going to be doing a lot of review of what we've been talking about the last 2 days. Tony and I have been using these last 2 days to introduce and do some practice problems with you about Taylor polynomials, approximations. So we're going to extend that learning to the alternating series airbound while also reinforcing those things that we talked about, as well as reinforcing a couple of things from earlier in Unit 10 as we begin to prepare for our AP review session starting next week. Every one of these lessons, Tony and I prepared some printed off handouts that you can use to create more problems than you could possibly do in one lesson. So you were able to download these materials, follow along with us, do the problems with us. And then you're also going to see a lot of other problems on that we don't get to that you can do for practice after these sections. And our really good friend Tim God always types up detailed solutions and posts them in the same Dropbox at the end of each evening, so we can check your answers as you go. So where do you find those materials? Well, under each one of our videos, the exact same hyperlink. If you click on that link, you'll get a folder shared with you by Isaac Newton, and you'll find all the materials for that day's lesson. So it's a good place to print those off, follow along with us, and then go back later and see how you did on the extra problems that you try out. Each day we introduce ourselves. By now, I hope you know who I am. I'm Brian Passwater, teacher at Speedway High School. But this week I've been trying to share a couple of other little tidbits about me that maybe you wouldn't know by watching these videos. And so today, the what do you not know about Mr. Passwater that you should know is that I was the 5th grade spelling bee runner-up at my school. And I want to point out 2 things about this. Number 1, it was a very competitive field, so I'm very proud of that runner-up. Number 2, I still remember the word that I missed, that I lost on. I'm not going to say it on the air because I'm a little bit ashamed at this point in my life that I could not spell that word in 5th grade. However, if you see me out in public ever, if you come up to me, I promise you, if you ask me about it, I will tell you the word that I lost on. And then finally, to show you how proud I am of this, or maybe how sad this is an important thing in my life, I don't know which one. This is actually a screenshot of the signature line of my email. So underneath my name and every email I send out, this is what I have, right? A lot of teachers have what awards they've won from teaching or what things they've done that have been spectacular, what titles they have. Nope, I have one thing under my name, which is this, right? Benjamin Franklin, one of America's founding fathers, one of the world's great Americans, was known for a lot of things in life. He was one of the people who were important in crafting the Declaration of Independence, important in getting France to help us fight during the Revolutionary War, help create bifocals and public libraries and fire arms, and all these things he was sort of known for. But when he died, he only wanted one thing on his tombstone. He wanted to say Benjamin Franklin, printer, because being a printer was the thing that he was most proud of and wanted to be known as in his life. Well, I'm not sure on my tombstone one day just to say 5th grade spelling bee or up, but I think it'll make its way on there somewhere, unless I win some adult spelling bee along the way. So that's a little bit about me today, a fact that you really didn't care about, but maybe you probably should know. Upcoming lessons. So this is our last day of Unit 10, like I mentioned. Next week, Tony and I are going to be working together as we do 3 weeks of AP exam prep. So everything we do is going to be focused on just preparing you for the upcoming AP exams. And each week has kind of a different theme to it. So next week, all the themes are going to be all of these BC unique topics that are on the BC exam. So we're going to be reviewing Unit 10 on Monday, looking at just those tested topics, how they might appear on this year's unique FRQ problems. Looking at integration techniques, Euler's method, logistic row, and arc length. So it's going to be a really good week next week. Make sure you tune into those. We're going to have lots of good response style problems that might mirror or mimic what you might see on this year's AP exam. Speaking of the exam, we're going to keep posting the slide on here. That way you can slowly start to remember and think about how this exam is going to look. We know it's going to be 2 FRQs this year, a 25-minute problem and then a 15-minute problem that follows after that. And because we only have 2 problems to cover a whole bunch of units, we know the questions are going to have to be pretty interesting. They're going to combine a lot of things together, but also find ways that will eliminate the possibility of students being able to use Google or textbook or notes to cheat on the exam, right? And so they're going to have some unique questions where those things aren't going to be really helpful to you as you take the exam. So Tony and I will give you our best shot at creating problems that will then kind of mimic that experience for you. So today's warm-up comes from the AP practice problem that Tony shared at the end of yesterday's lesson. And here's the question here, and we're just going to jump right into it. this, that way we have more time to see additional problems. And so part A said p sub 2 is a second degree Maclaurin polynomial, and it's known that f of 0 is 1, f prime of 0 is 0, and then p of 1 equals 1/2. Find f del prime of 0. So it's kind of a different twist on what we've been doing, right? So the last 2 days we've been asked to make Taylor or Maclaurin polynomials based on some given information. Well, here they don't technically ask us to make the Maclaurin polynomial, but they did ask us to find the second derivative of f. And so here's how I would probably maybe tackle a problem like this. We have a lot of information, you're not really sure where to begin. I kind of think about what's important, right? So we're talking about a second degree Taylor polynomial, so that means that our n value is going to be 2. It's Maclaurin, which tells me the center has to be 0, right? Maclaurin polynomial is just a Taylor polynomial center 0 when we're making it for the function f. And so whenever I'm trying to make or use a Maclaurin or Taylor polynomial, it helps me to just write out that formula that is given to us in our notes on Wednesday, and that Tony reinforced it yesterday for Taylor polynomials. So any Taylor polynomial or Maclaurin polynomial is just going to be equal to f of the center, right? Remember our center was 0 plus f prime of the center times x plus f double prime of 0, x squared over 2 factorial. This would be the general form of a Maclaurin polynomial of degree 2, right? And so then we realize in order to create one of these, it's our job to figure out what all of those f's are. We have to find all of those f prime, f double prime, and if we can get numbers for all of those, we're able to plug in those values. That creates our Taylor polynomial. Well, in this case, we didn't ask you to find a Taylor polynomial, but we did tell you some information. We told you that f of 0 is 1, so that means that p sub 2 of x is going to be 1, and then f prime of 0 is 0. So that term right there is going to go away. So all we have left is this. Now the problem is we don't really have a way to find f double prime of 0 right now because number one, we're not given a function, or we're not given a formula to find the derivatives like we were yesterday. However, we were told that for the particular polynomial, if we plug in 1 for x, our answer should be 1/2. And so I could use my function here. If I plug in 1/2 for p sub 2, and I plug in 1 for x, we're going to get this. That 1/2 equals 1 plus f double prime of 0 over 2. And then now we can solve this problem for f double prime of 0 pretty easily. If we subtract 1 from both sides, we get negative 1/2 is going to equal f double prime of 0 over 2. And then multiply both sides by 2, and we're going to get f double prime of 0 equals negative 1. That's what we're trying to find. F double prime of 0 is just going to be negative 1. Now, I know this problem didn't ask us to find the actual polynomial. I'm going to go ahead and write it down since we were practicing this yesterday. The p sub 2 would have been 1, and then minus x squared over 2. All I did was plug in the negative 1 here for our f double prime. That's why we got a minus sign there. So our second degree polynomial would be 1 minus x squared over 2. And that's going to help us solve part B. It says let's find p prime of 0 and p double prime of 0. Well, let's start by just writing down what p prime of x would be. Well, since we already found p of x above, the derivative of this, the 1's going to go away, and then the negative x squared over 2, the 2 would come down in front. It becomes negative 2x over 2, which is just negative 1x. And then we want to find this value at 0. By plugging 0 here, guess what we get? Just 0. And then also once we find p double prime of 2, well, let's go ahead and find p double prime of x first. Well, the derivative of negative 1x is just negative 1. That means that p double prime of 0, well, we don't even have an x value to plug it into, so the second derivative at 0 is also going to be just negative 1. So we answered the first part of the problem. Now it says, does p of 2 have a relative minimum, maximum, or neither at x equals 0? Give a reason for your answer. Well, normally when we see things like minimums and maximums, relative mins and relative maxes, our first instinct is probably to think about that first derivative test. Find critical values, then do a little number line, a sign chart, look for a change in sign, the derivative, and then explain it using proper explanations. But whenever a question asks you some information up front, there's usually a reason why they ask you that, because they're going to ask you a second question later on. So here, we can figure out whether it's a relative minimum or maximum using an older idea from Calc AP that we don't use a whole bunch called the second derivative test, right? We know that p prime equals 0, so that's going to be a critical value. And we also know that p double prime is going to be negative 1, which tells me that our graph is going to be concave down. We have a graph that has a critical value of slope of 0, but also a second derivative is negative, which means it's concave down. In those two situations, we're going to create for us a relative maximum at x equals 0. And our reason is going to be because our first derivative is 0 and our second derivative at 0 is negative, right? It's less than 0. And that will be enough of an explanation. Now, really what we were explaining here was just the exact explanation of what the second derivative test tells us. We can mention the second derivative test, or we can just give the value to show that it's a critical value because the derivative is 0 and it's concave down because the second derivative is less than 0. And then the part C of this problem is going to tie us right into today's lesson, which is let's use our Taylor polynomial that we created here in part A to approximate f of 1/2, right? Remember, we have this function f that we don't really know what it is. We don't even know much about f, do we? They never gave us an equation for f. They never told us a formula to find all the derivatives. All we really know about f is f of 0, f prime of 0, and f double prime of 0. We only know 3 tiny things about it. So it's kind of this unknown function. So how would we approximate it? How would I plug 1/2 into a function that we really don't even know? Well, that's why we use Taylor polynomials. Any function that we create Taylor polynomial for, we know can be approximated by plugging in the same value into our polynomial. Well, our polynomial was just 1 minus x squared over 2, so it's going to be 1 minus 1/2 squared over 2. And then a little bit of arithmetic will give us 1 over 4 divided by 2 there, and that's going to be 1 minus 1/8, or in this case 7 over 8. So it turns out that f 1/2, our best approximation based on what we have known to us, is going to be about 7/8. Now the real question becomes, is that approximation even any good, right? We don't even know what f is, so we have no way of knowing whether this is a really good approximation or some terrible approximation, but it's probably in our best interest to have some sort of idea when we're approximating, to know how decent or how close our answer that we come up with is to what the real value is, right? So to give you a little bit of insight into this, we don't know a whole lot about f, right? I do know that f of 0 is 1, so it's going to go through this point. I also know that the slope of f is going to be 0 right there, and the second derivative is negative 1, so f is going to be some function that's going to be concave down or something. I'm just making up a function for x. It may not look like this, but we know that it goes to that point, it has a horizontal tangent, and it's concave down at that point. And then we created a Taylor polynomial, right? P sub 2, that is going to be 1 minus x squared. Well, that graph of 1 minus x squared looks like this. This is what p sub 2 of x is. And so we were interested in knowing f of 1/2, right? Which might be somewhere over here, and we couldn't find it directly, so what do? We plugged in 1/2 into our polynomial, and we're just hoping that that value is pretty close to the function of f, right? Well, today we're going to learn there are some cases where we're able to not know the exact error, but we can bound it a little bit, right? We can at least say, okay, I don't know exactly what the true answer is, but I know that it has to be at least within this much of what we came up with. So it gives us a lot better idea of how decent our approximations are. So that's going to lead us into our overview today. So what are we going to do today? Well, we're going to introduce this idea of the alternating series error, and then we're going to hopefully connect some of the previous topics of Unit 10, like geometric series, harmonic series, and even the Taylor polynomials today, to reinforce those testable ideas in the middle of this new concept. So what do you need to know? Well, hopefully you can remember a little bit about alternating series and geometric series. So we're going to use those, as well as the last 2 days of Taylor and Maclaurin polynomials. And by the end of the lesson, we'll see problems like approximate sine of 0.2 using a third degree Taylor polynomial centered at 0. By the way, if it's centered at 0, that should remind us, oh, that particular Taylor polynomial could also be called a Maclaurin polynomial. And then determine an error bound of this approximation from the true value of sine of 0.2, meaning once we make our approximation, how do we know how decent of an answer it is? So to do that, we'll look at one of the series that we've learned before. This is the alternating harmonic series, right? It's 1 minus 1/2 plus 1/3 minus 1/4, and it goes on and on and on. And this value is going to approach or equal some number L. We know that the series converges by the alternating series test, right? Remember that? A series is alternating, which it is. And then in this case, we can kind of think about the series as negative 1 to the n minus 1, according to this, times 1 over n, which means that our a sub n in this problem is just 1 over n, right? And we know that an alternating series converges if the a sub n terms approach 0. Well, lucky for us, the limit as n approaches infinity of 1 over n does equal 0. And if the terms are decreasing, well, we do know that 1 over n plus 1 is always going to be less than or equal to 1 over n for all of our values as long as n is 1 or greater, which is the exact index of our series. So this meets all the criteria of an alternating series test, and so we know it converges. And so it converges to some value L, which in this case we don't really know. Some of you might actually know this converges to. In the real world, we do know what it equals. And if you've been learning this in class, you might have actually talked about what this equals to, but we're going to hold off on that now. We're going to keep the mystery that let's just assume it approaches some value. We don't quite know what that value is. And so what if we try to create some partial sums of this, right? We start adding these terms out, right? Well, S of 1 is just the first term, that's just going to be 1. And then S of 2 will be the sum of the first two terms, so 1 minus a half, which is a half. And then S of 3 is the sum of the first three terms, S of 4, S of 5, on and on, right? And so we can see these partial sums kind of approaching some value, and they're getting closer and closer to some mystery value of L. Well, we can't possibly add up an infinite amount of these things, right? It's going to take forever, literally. So what if we wanted to stop after 7? After 7 of these, we add up these fractions, and we got 319 over 420, and this is sort of our approximation, right, of what the true series is. But then we get curious to know, is that even close to the real answer? Is that, how far off is it from what the real value of L is? Well, I went ahead and plotted these partial sums, and this dotted line in blue, this actually is the value of L. We can see each time we add another term, we get a new partial sum. It's sort of bouncing back and forth. That's the alternating nature of this. But each time it bounces, getting a little bit closer and closer and closer to that magical line of L, what the true series adds up to. So we calculated S of 7 right here, and we want to know how far is this from the true value, and we call that the error. Whenever you approximate something using a Taylor polynomial or the first few terms of any series, we know it's not going to be the exact value of the entire series, so there's going to be some kind of error involved, right? And the error is just going to be the difference between the true value, which is L in this case, and whatever partial sum we did. So the error of S of 7 is just going to be where the true value of the whole series is minus S of 7, and we're going to take the absolute value of that. That way we don't have to deal with any negative values. Well, that's going to be our error. We want to know how big or how small is that error. Well, we could, in this case, know exactly what the error is since we know what L is, but in many cases we don't know what L is. On our previous example in our warm-up, we were approximating F. Well, we don't know what F of 1/2 is because we don't even know what F is, right? And there are a lot of series that even though we can find partial sums, we don't even know what the true answer is. We don't know able to figure out what L is, even though we know they converge, right? And so it will help us to know how decent of an approximation we have. Well, to do that, what's missing in this picture are all of these A sub x. These are just the S sub it, the partial sums. Well, A sub 1 is just the same as the first partial sum, isn't it? S sub 1 is 1 as the first term. Well, S sub 2 is here. Well, how do we get down there? Well, what we really did was we subtracted A sub 2, didn't we? Remember, 1/2 is my A sub 2. A sub 2 is just 1/2. A sub 3 was 1/3. A sub 4 is 1/4. And it's going to continue, right? So to get from my first partial sum to my second one, I had to subtract A sub 2. And then get back up to my third partial sum, we had to add the third term, and then we're going to subtract the fourth term. It's going to keep going back and forth. So those distances between those partial sums are just going to be the absolute value of that next term, right? And so here's F sub 7. This distance right here between here and L, that's going to be our error, right? We want to know how close is F sub 7 to the true value of L. Well, we don't know exactly how far it is, but what we do know is that the distance between S sub 7 and S sub 8 is just going to be the term A sub 8, right? A sub 8 is just how far we go from S sub 7 to S sub 8. And we can see that the error between S sub 7 and the true value, this little gap right here, is smaller than the distance between S sub 7 and S sub 8, which means our error here is going to have to be less than A sub 8. So we knew what the eighth term was. We knew that our error bound, how close our answer is to the true answer, is going to be certainly less than, in some cases, equal to that next term. So this is going to be the setup for the alternating series error. That if we have a convergent alternating series where A sub n's are positive and each term is less than the previous term, this is kind of a little condition that we always want to overlook. Whenever we have a theorem or a definition, it's really easy to overlook the conditions. And then all of a sudden, the College Board writes a really unique or neat question to check whether you're thinking about conditions of theorems, and then they'll throw something in there that doesn't meet this criteria, and all of a sudden it seems like the theorem fails. Like, wait a minute, it's a contradiction. Well, it's not a contradiction. This only works when the terms are decreasing in nature, right? Sometimes we can guarantee it. So let's go back using this idea that says, okay, if we have a convergent alternating series and the terms are decreasing, then the error is going to be S. Remember, S is the true sum of a series minus our partial sum S sub n. So we add up n terms, 1, 2, 3, 4, 5, however many you want. The difference between the true value and that approximation, which is the error, should be less than or equal to the next term in the series. So looking at our alternating harmonic series that we just did, right? We have negative 1 to the n minus 1 over n equals this kind of mystery value of L, right? And we already showed that S sub 7 was just adding up the first 7 terms, which was 319 over 420. And I went ahead and gave us the decimal approximation of that using my calculator. I cheated a little bit, but it's about 0.7595. And according to our alternating series error, if I were to take the error, we know that S sub 7 is not the true answer. The error is going to be whatever L is the true answer minus what we came up with, which was S sub 7. This should be less than or equal to the next unused term, which would be the A sub 8 in this case. And remember, since we were doing our alternating harmonic series, A sub n is just 1 over n, which means that A sub 8 is just 1 over 8, which happens to be 0.125 as a decimal. So here's what we're claiming. We're claiming when we calculated the first 7 terms, we came up with an approximation of about 0.7595. I'm going to round a little bit. And we don't know how close that is to the true answer, but according to the alternating series error, it has to be within 0.125 of the true answer, meaning the L has to be within 0.125 what we came up with. Well, if we were to subtract 0.125 from our approximation, we would get 0.6345 approximately. And if we were to add 0.125, we would get about 0.8845. So what we're claiming according to this theorem is that the true value L has to be in there somewhere. It should be somewhere between 0.6345 and 0.8845. And it turns out it is because we know what L is. The alternating harmonic series, the way it was written there, would be equal to the natural log of 2. And the natural log of 2 is 0.69314. It kind of keeps going, right? And so notice 0.69314 is actually going to be right here somewhere. So it turns out that the true value really was within that error bound that we just calculated. And written another way, the true value S or L minus our approximation is the saying L n of 2, that's the true value, minus S of 7, which was that fraction, was 0.066. So this was the exact true error of our approximation. Using the error bound, we knew that the error had to be less than or equal to 0.125, which in fact it was. It was about half of that actually. So why would we do this when we actually knew exactly what the series added up to? Well, this is just giving us an example of how the error bound works. In reality, there's a lot of series that we don't truly know what they add up to. And so if you don't know what it adds up to, it's really helpful to know how close your approximation is when you don't know the true answer. So let's take a look at a couple of examples together to kind of put this into more concrete examples. So example 1, let's approximate this alternating series, negative 1 to the n minus 1 over n squared, using the first 3 terms. So we're going to use the first 3 terms. And then we're going to show that that approximation is within 1/10 of the true sum of the series. Well, let's go ahead and start by writing out the first couple terms. In this case, a sub n, right, that's the non-alternate part, is just 1 over n squared, right? So the first 3 terms, we're plugging 1, 2, and 3 to here. If I plug in 1, we get negative 1 to 0, which is just 1 over 1 squared. If I plug in 2, we're going to create this alternating piece here, and 2 squared at the bottom. And then if I plug in 3, we're back to a positive 1 on top over 3 squared. So the first 3 terms just becomes 1 minus a 4 plus a 9. And then I'm wondering, okay, first of all, how big is that number? I believe if my math is correct, that's about 31, or exactly 31 over 36. When I say my math is correct, I kind of wrote it down on a piece of paper here this morning to make sure I would mess that up, but I'm pretty sure that's what it was. I was a little early this morning, so my math could have been bad. This is what we get for the first 3 terms. And we want to know, how can I show that this is within 1/10 of the true sum? Well, this is an alternating series, right? And the terms are going to be decreasing each time. 1 over n squared is going to be a decreasing function. And it does converge by the alternating series test. So it meets all the criteria. And so we know that the error of this series is going to be the true value minus what we approximated, right? S minus S of 3. That should be less than or equal to the next term, which in this case would be A sub 4. Well, what is a sub 4? Well, if a sub n is 1 over n squared, then our error is going to be less than or equal to 1 over 16. And guess what? That error bound is in fact less than the 1/10 that we were asking about. So on an AP problem, I'm going to ask you to do something with the error like this. We're really looking for two things. Number one, we're trying to see that you're the proper error form, right? The proper error bound. So that absolute value of s minus s sub n, whatever that example would be in your problem, is important to show. You're showing that you're calculating the error, and then you're also connecting it to that next term, right? So we know the error is less than or equal to 1/16. That's a big important part. It's the first thing we're looking for. And then also we're trying to make sure that once you find your error bound, that you connect that back to what the problem wanted, right? We wanted to show that our error is less than 1/10. So whatever error bound we come up with, it should be less than whatever error bound they were asking us to parity. So that last step of saying that our answer is less than 1/10 is going to be the second piece of what those FRQs typically want. So let's look at one kind of backwards now, right? Instead of saying what is the error bound, what if we said how many terms would we need to create a specific error bound? So how many terms are needed for this alternating series to be approximated to within 0.01 or 1/100? So we're trying to guarantee that our error s minus s sub n. Now we don't know what n is yet, but we want to make sure that that error bound is within 1/100, right? Well, how do we calculate error bounds? We calculate error bounds by using the first unused term, right? That next term in our approximation that we don't include, that will be our error bound. Well, in this case, a sub n, that's our general form, is just 1 over n squared because the alternating part is just the -1 to the n plus 1. And really, I want to figure out when that term is less than or equal to 1/100th. What value of n would create a fraction that's less than 1/100th? Well, if we think about our factorials, 1 over 4 factorial is just 1/24th. Well, that's certainly not less than 100. 1 over 5 factorial is equal to 1 over 120. And guess what? That does kind of meet our criteria, right? That we're getting a term that's less than 1/100th. Now, the trick is, how do we answer this question? Because we know that when n is 5, we create a term that's less than 100. So our first instinct might be 5, right? If I have 5 terms, then it would be an error less than 100, which is true. But remember, when we're doing error bound, this is not actually our last term. This is our first unused term, right? And so it's that fifth term that creates the error bound, which means we only needed to actually add up 4 terms, right? If we add up the first 4 terms of the series, it would have been 1 over 1 factorial minus 1 over 2 factorial is an alternating series, right? If I add up just the first 4 terms, s sub 4, then the error, right, of that series would have been equal to the true value minus s sub 4, and it would have been less than or equal to the next term, which would have been a sub 5, right? Which is 1 over 5 factorial. And since this value is less than 1/100th, we only needed 4 terms in this case. If we add up the first 4 terms, then the fifth term is the first term that is less than that coveted 1 over 1. Let's look at maybe a couple more quick examples. I want to have you try some on your own and see if we can kind of put this together. So consider the geometric series. Now I know we know the sum of a geometric series. We're going to kind of forget that for a moment. Consider the geometric series 4 minus 2 plus 1 minus a half, on and on and on. And the first 5 terms, so s sub 5 add up to 11 over 4. These first 5 terms are going to be 11 over 4. Use the alternating series error bound to determine the maximum error. Meaning I know this is not the true sum, but maybe we can use that. I know it has to be within a certain amount, right? Use the alternating series error bound. And we know we can use this because this is a convergent series. It's alternating. The terms are decreasing and approaching 0. So the maximum error bound says that the error, right, is going to be equal to the true value minus our approximation, which needs to be less than or equal to the next unused term of a sub 6. Well, a sub 6 is just 1/8, right? And so we're claiming that the error in this case is less than or equal to 1/8. So that means that if we think about what our approximation was, our s sub 5 was 11 over 4, then we're claiming that this is within 1/8 of the true value. Meaning if I were to add 1/8 and subtract 1/8, the true value has to be somewhere between there. Well, if I subtract 1/8 from this, you end up getting 21 over 8, which is 2 and 5/8. If we add 1/8 to this, we get 23 over 8, which is just 2 and 7/8. So really what we're claiming is that the true value of s is somewhere between those two values, right? Our maximum error is 1/8, which means the true value has to be between 2 and 5/8 and 2 and 7/8, which is a pretty good window, right? We've got it pretty narrowed down. And we can verify this because it's an alternating series, right? It's an alternating series where a is equal to 4 because it's geometric, and r, what are we multiplying by each time? We're multiplying by -1/2. And we know from our geometric series study, see how we're tying all these things together? Once we learn all these topics, they really tie in well together and give you a better idea of this big picture. That's what the exam is going to most likely make you do, is make you make these connections between all these little things we've been learning, between P series and alternating series and geometric and polynomials. So we can't just learn a couple of rules and formulas. We have to understand these concepts at a deeper level so we can make those connections with so the geometric series, the sum, our formula is a over 1 minus r, which in this case is just going to be 4 over 1 minus -1/2. And if we reduce that, 1 minus a half is just 3/2, which means the true sum, the true value of s is just 8/3. And 8/3, if we make that into a mixed fraction, is just going to be 2 and 2/3. Well, guess what? 2 and 2/3 is right around here somewhere, right? So again, our alternating series error bound did in fact come through for us. And of course it's going to come through because as long as we meet the conditions, we know it has to be true. That's the proof of the theorem. One more example that I'm going to kind of leave off for right now, but I might encourage you to try. It's a neat little example that kind of ties back into a couple of things. Number one, geometric series, but 2, forward series with x. And it does kind of lead us back into this idea of Taylor polynomials and Taylor series as well. So it's a really neat example, but I want to give you a chance to try some of these on your own. So we're going to go to the check for understanding, and we're going to try a couple of these. And so this is really a good reinforcement of the last 2 days lessons. We're going to take it one step further in a minute. But I want to give you a second, just make sure we can remember how to do those things from the last 2 days. And so take a minute and see if you can construct a third degree Maclaurin polynomial. So think about what these keywords are, right? Third degree Maclaurin for f of x, where f of x is sine of 2x. And once you come up with that, use that to approximate f of 1. Now, because we're talking about sine of 2x, I realize you can just take a calculator, right? And just type in, sine of 2 times 1 and you get an answer. But we're going to sort of put our mindset in a situation where we don't either have a calculator or think about examples where maybe we don't truly know what the function f is. So it's something to type into a calculator. We're just doing this example with sine because it's something you're familiar with and we can verify easily, right? So take a minute to do that. And then once you're about halfway through, I'm going to play some nice work music from our friend Kareem. That way you'll know you have about 30 seconds left. So once you hear the music, you're going to have 30 seconds to finish out this construction of your Maclaurin polynomial. So try that and then see if you can plug in a 1 for x and approximate that value. Awesome. I hope you guys did well on this problem. I want to thank Kareem again for our work music. One of the things I've been blown away with as Tony and I have been doing these lessons is all the talent that we have out there. Some of the memes that you guys have sent me have been hilarious. I can't post some of them on here, but then the music that you guys are sending in have been awesome. We still have a couple of more people have sent in music. So if you're wondering, man, I haven't heard my music yet, Tony and I are going to get them worked in. So don't worry. We've been blown away by that. So we're going to get those in there so we can share all the talent that's out there. So let's take a look at this first part of the problem. It says construct a third degree Maclaurin polynomial, right? So it's a third degree meaning n has to be 3, and then Maclaurin means that our center is going to be 0. And Tony did a really neat job yesterday of giving the analogy. We're putting together our IKEA furniture when you're building a Taylor or Maclaurin polynomial. I like that analogy. On Wednesday we talked about what those polynomials are doing, right? We cloned my dog Buddy to kind of give us the image that a Maclaurin or Taylor polynomial polynomial is trying to clone a function, right? And then how to do that, the process is you buy the kit and build it like we would IKEA furniture. What helps me as I do this is to realize that my function f of x can be approximated using a third degree polynomial. And I like to write the general formula out each time because I feel like it gives me something concrete to look at to help remind me what values I need to find, right? So if we're going to make a Maclaurin polynomial of degree 3, it's going to be equal to f of 0, the function at 0, that's our center, plus f prime of 0 times x, plus f double prime of 0, x squared over 2 factorial, and then f triple prime of 0, x to the third over 3 factorial. So we're going to create this polynomial. Remember, our job is to come up with all of those values of f. That's what we have to find, are all those f values. And once we find those numbers, we plug them in, and that is our polynomial. And so I did a really nice job yesterday of organizing this for us, that we know we're going to have to find all these derivatives all the way up to the third derivative. So f of x is just sine of 2x, and then f prime, we're going to take all these derivatives. Well, if we use the chain rule of our derivatives, it's going to be 2 times cosine of 2x. All that stuff from AP about taking derivatives and intervals is still pretty important. And then the next derivative using chain rule again becomes negative 4 cosine sine, right, of 2x. And then the third derivative, the last one that we need, is going to end up being negative 8. Now we're back to cosine of 2x. And we want all those values at 0, right? We got to find f of 0, f prime of 0, f double prime of 0. Well, f of 0 sine of 0, that's just going to be 0. And then f prime of 0 is 2 times cosine of 0. Well, cosine of 0 is 1, so it becomes 2 times 1. F double prime of 0 is negative 4 times sine of 0. That brings us back to 0 again. And then finally, the third derivative at 0 is negative 8 times cosine of 0, or negative 8. And so now we found all those f values, which means that our polynomial is going to be f of 0, that's 0. I'm going to write that down. F prime is 2, so we're going to get a 2x here. F double prime is 0, so we don't need to write this term down. It's just going to cancel out. And then the third derivative is negative 8, which creates a minus 8x cubed over 3 factorial. Now, maybe we want to reduce this. You don't have to reduce things on response problems that are numerical, but sometimes the teacher in us, it's hard for us to leave things unreduced. 3 factorial happens to be 6, and 8 over 6 is just going to be 4x cubed over 3. So our third degree polynomial is just going to be 2x minus 4x cubed over 3. And if we want to approximate f of 1, then we can approximate f of 1 by plugging in 1 for x, and that's going to be 2 minus 4 thirds, which happens to be, if I reduce this, what is that, 2 thirds? Is that 2 minus 4 thirds? Is just 2 thirds? 2 is 6 over 3. So it's 2 thirds is our approximation. There we go. That is our approximation for sine of 2x when f is 1, right? F of 1 is like plugging 1 in for x. That's going to be sine of 2. Now, there's a second part of this practice problem that says, okay, if you had done a full year of Calc, we didn't have to reduce topics. We get this idea of power series and Taylor series. And it turns out that the function f, which is sine of 2x, can be represented by this whole series of terms, which is this. And it turns out that our polynomial will keep creating the first couple of terms of this, meaning if I were to expand this, plug in different values, what we would end up getting is going to be 2x. Say that was our first term of our polynomial. If I plug 2 for n, we're going to end up getting 2x to the third power over 3 factorial. That's what we actually got. 2x cubed is just 8x cubed. And if I keep going with this expansion, we get sort of this nice alternating series, right? That's going to kind of keep going there. And so we want to show that our approximation in the first example here was within 1/2 of the true value. Well, this series is alternating. The terms are going to be decreasing in nature, so we're going to meet that requirement. And it does converge. We know that. And so we could use this alternating series error bound to approximate how bad our error is, right? Our error, we know, is going to be less than, or actually it's going to be equal to, sorry, the true value of s minus our approximation. Well, if we're using this series right here for our approximation, we only use the first two terms of the series, right? I'm not going to connect to the series idea. We use n equals 2 the way this was written. So we actually found s of 2 of the series, and that should be less than or equal to the next unused term of the series, which happens to be this guy right here. So we know that our error that we came up with is going to be less than or equal to this term when x was 1. Remember, x was 1 in this case, and so it's going to be 2 to the 5th power over 5 factorial. Well, it turns out 2 to the 5th power is just 32, and 5 factorial is 120, and indeed that value is less than 1/2. Obviously, 32 over 120 has to be less than 1 because 60 over 20 is equal to 1/2, right? And so 32 over 20 is going to be significantly less than that. So by using the first two terms, we just approximated sine of 2 in this case to within 1/2. Now, this problem, that's not a very good estimation, right? If you think about a sine graph can only go up to 1 as the highest sine can attain, right? And then go down to -1. So the entire span of the sine, the entire range is just 2, right? It goes from -1 to 1. And we came up with an approximation that we can guarantee is within 0.5 of the true answer. Well, if you're only approximating sine to within 0.5 of the true value, you can almost guarantee that without even doing a series at all, right? So only doing two terms probably wouldn't be enough for us to feel very confident about our answer. But if we kept going in a couple more terms, we could guarantee our answer to be really close to the true value. The other practice problems, we're not going to have a chance to do all of these today, but I do want to look at just one of these. That's the last practice, number 4. It says the function of cosine. We've been dealing with creating some polynomials for cosine. Again, the power series for cosine, which we're not going to have to test on this year, but this is the expanded series for cosine. Now, we could create some Taylor and Maclaurin polynomials, and that would be a completely valid question on the exam. And it turns out the Taylor and Maclaurin polynomials centered at 0 are just going to create the first few terms. If we created a Maclaurin polynomial of degree 4, it would be the first 3 terms of this. If we did one of degree 6, it would create the first 4 terms of this. And so we know that when you make a Taylor polynomial and Maclaurin polynomial, you're just creating the first few terms of the true overall series. And so we're going to show that the second degree polynomial, Maclaurin polynomial, is just equal to that, right? So we're going to confirm that that's true. Well, let's think about making a second degree Maclaurin polynomial for f. Maclaurin means we're centered at 0. And so our general formula is that p sub 2 is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial. And in this case, we know that f is just cosine. And so just like before, to find all of those f values, we have to take some derivatives here. So cosine derivatives negative sine, and then the second derivative becomes negative cosine. And if we want to find these values at 0, well, cosine of 0 is just going to be 1. Sine of 0 is 0, a lot of unicircle, right? And then f double prime of 0 is negative cosine of 0, which gives me -1. So if we're going to build our polynomial, we know that p sub 2 of x is going to be our f of 0, which is 1. If f prime is 0, this term is going to go away. And if f double prime is -1, we get this minus x squared over 2 factorial. So building our Taylor polynomial, we can in fact confirm that our second degree Maclaurin polynomial is just going to be the same as the first two terms here. If we did a 4th degree or a 6th degree, we would keep getting the rest of these terms. This really leads us to the idea of power series and how powerful those are and calculating things like sine, cosine, all those ugly functions that we mentioned on Wednesday. So today we looked at how the enduring understanding is that applying limits, partial sums, can create an idea of determining a finite sum of infinitely many terms. It's a fancy way of saying for some series that converge, we can figure out what it converges to by looking at some partial sums. The Taylor polynomial can allow us to approximate values again. And then for a convergent alternating series with decreasing terms, we can determine an error bound when approximating values. That was the alternating series error. Now notice that error bound only worked with alternating series that met that criteria of the alternating series test, right? Well, not every series alternates. You can create lots of Taylor polynomials or lots of Maclaurin polynomials that don't alternate, in which case we can't use the alternating series error bound to figure out how good of an approximation it is. Luckily, we have a lot of other ways of approximating error bounds as well, right? In the normal BC course, there's an idea of Lagrange error bound, which applies to any Taylor polynomial, whether it's alternating or not. That comes directly from Taylor's theorem. We have some other ways of bounding errors, like with integral error bounds, some other kind of neat ideas. But the alternating series error bound is a pretty nice, clean, simple one that we're going to share with you so you can understand kind of the next step of Taylor polynomials. A polynomial, a Maclaurin or Taylor polynomial is a great way to approximate a more complicated function or even a function we don't know explicitly, but it doesn't do a lot of good to approximate something unless you have some idea of how decent of an approximation it is. So some of the common errors is that some students will try to apply this to things that are not alternating. We can't do that. And that we have to remember that it's based off of the first unused term. So it's not based off the last term you use. It's based off of whatever term would come next if you kept going with the polynomial series. So your AP practice problem today, this is the last one that you're going to get because starting on Monday, we're doing review lessons. So the zeta function is there. It's given by the sum of 1 over n to the s, which is the same thing as the product of the primes of the expression 1 over 1 minus p, where p is a prime number, the negative s power. And all you have to do for Monday is for that zeta function given above, please show that all non-trivial zeros of that function have to be of real part 1/2, right? So a pretty straightforward problem. Actually, I'm just kidding. This is called the Riemann hypothesis. This is what I have tattooed on my arm that I shared up on Monday. You're not going to be able to solve this. If you could, you get a nice $1 million prize as a $1 million bounty on this problem. But in fact, there's no homework for you this week. Just enjoy the weekend and get ready to join us live on Monday as we go into full-fledged AP exam prep mode for Calc BC. We have been doing tweets each day. I'm going to share these real quickly. And if you're a teacher and you have a Twitter account, take 30 seconds today. Go on Twitter, and I know that you are proud of your kids. So go on Twitter and tweet out what you're proud about with your AP students. And make sure you include that hashtag AP Teachers Rock. Tony and I are searching that hashtag to find tweets to use each day. And if you're a BC student and you're watching this, you must be amazing because you're listening to Tony and I every day, at least some days. But means you must have an amazing teacher. So hop on your Twitter account and tweet out what you love about your AP Calc teacher, and then Tony and I will read more of these on the air. So our AP Teachers Rock, Ms. Listen at Northwest High School always helps us stay prepared for our tests. She makes AP Calc BC seem so easy. That is not an easy task. BC is a tough subject, as we've seen here this week. So kudos, Ms. Listen. And I love my students. In creating calculus summaries for review, one group's worth of clips of my Captain Earth Space buddy enjoying the integrals. He was so happy he took a selfie with their work. AP Students Rock. Man, I wish we had a picture of that buddy. Oh wait, we do. We have a surprise visit. Captain Earth Space buddy, here he is, taking a selfie with some of these student projects. So well done to all of you out there who are doing that. And again, as we end up today, if you need some tech help, you know what that does, please reach out to collegeboard.org/tech, and they can help you get the information or the devices that you need to watch these videos, get resources on the AP Classroom, or even taking these online tests. So with that, thank you so much for watching. Don't forget, next Monday, coming up, same time, same place, Tony and I will be together, hitting up some awesome BC Calc review. We hope to see you there on Monday, 9 a.m. Eastern time.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Starting at some value of n and going on forever, that the terms are consistently decreasing, right? That each term is less than the term before it. Well, we can check that fairly easily as well because we know 1/2 power is the square root. So if I plugged in n plus 1, I do know that the square root 1 over the square root of n plus 1 is certainly going to be less than or equal to 1 over the square root of n for any n value greater than 1. So we met both conditions. So that way we know that this series converges by the alternating series test, right? And so because this exam is all for response, the communication and the notation is going to be quite important, right? So if we were just doing a multiple choice type question, we could easily look at this problem, come to the same conclusion, maybe not show all of the work as detailed, but for FRQs on an exam, we're looking for that you're checking those conditions. We want to see that you clearly have those two conditions laid out that will allow us to reach that conclusion. We can't just assume converges by the alternating series test without first communicating why we know it converges. So the second one, this one's not alternating, but it certainly looks like a p-series, right? We have n to a power. So this is a p-series where p is just 3.5. Remember, one of our topics that's tested this year is going to be the p-series test, and the requirement for the p-series test is as long as our p-value is greater than 1, right? It can't be equal to 1, it has to be greater than 1, then a p-series will converge. This series converges by the p-series test. So already, for just one part of this question, we've already been able to introduce 2 of the topics from this year's exam, right? We've done alternating series test, which we did, as well as p-series test, all in one problem. So one of the things you might hear Tony and I mention throughout this these next several weeks is we like to classify for our own students these questions. So sometimes we call them like level 1, 2s, and 3s in terms of difficulty. I'll probably use the terminology 3s, 4s, and 5s, meaning when we see a question, we'll give you an idea of what we think a student's score would be if they could do questions like this. So for example, part A, if you're trying to get a 3 at least in the AP exam, which I hope you are, right? You guys all get 3s, 4s, and 5s, especially after these next several weeks with Tony and I. But if you're trying to get a 3 on the exam, you're going to have to be able to do problems like this. These are the kind of questions that will show that students can get a 3 on the exam. You have to remember some of our information of our different tests, but then more importantly, you have to be able to communicate that clearly and execute it on the exam, right? So some problems that get more challenging are what separate a 4 and what separate a 5 on the AP exam. But this is going to be what it takes to get a 3. So as we do these problems, we're going to lay out for you the differences between the questions, so you can see where those distinguished, those little nuances go. And we typically see that as the FRQs go deeper, part B, C, we start to see a stretch of other problems. So this is BC1 part B, and it looks a little bit different than what we've seen. It seems like it might be a little bit more challenging than just a regular level 3 question we just saw.
It does. Maybe we'll call this a 3.5 if there's such a thing at this point. But we still have the idea of these seemingly p-series behaved kind of expressions a n and b sub n. If we assemble our first series, so we've got this summation as n goes from 1 to infinity of the a sub n, which is -1 to the n over n to the p minus 2. Now we're not going to deny the fact that this denominator has that p-series look, but we need to remember from part A as well that we have this alternating version of this p-series. So that kind of gives us a little bit more leeway as to what this p minus 2 value can take on, what that exponent has to be. And using the information that we gleaned from part A, we know that we probably deduce that this will converge if that p minus 2 was something that's positive. And I think we had it equivalent to a 0.5 from part A, but we could even take a little bit more leniency with that and get closer to 0 as long as we had this positive exponent. That's only because we have the alternating component. We have this conditional convergence up until p minus 2 being 1, of course, but that's fine. Whether it's conditionally convergent or absolutely convergent, we're just looking for some type of convergence period. So this is going to mean that p is going to be greater than 2. So we know that those are the p's that are going to allow the first series to converge. Now if we take a look at the second series, the b sub n series, so we'll assemble him. We want to make sure that we're very alert to the fact that this is not an alternating series. It does have that negative sign on top, but it just doesn't have the rest of the components that would indicate that this is alternating. This is probably a series where all the terms perhaps are negative. So in this particular case, we have probably, I would say, a little bit more strict set of guidelines that would allow this to converge, and that is that 6 minus p, the exponent of that n that's in the denominator, has to be strictly greater than 1, and that would not include the 1 in that case. Right? We need this to be a p series where the exponent is going to be larger than 1. So if we were to solve this, let's say we add p to the right and then we subtract 1 over to the left, we would see that p is going to be less than 5 in that case. Right? Well, now we have to answer the question. We want to find integer values of p so that both of those series are going to converge. So we can start to kind of write up our conclusion, and we say, well, all right, well, both series converge, and it looks like I need to consider sort of the intersection between p greater than 2, p less than 5, but at the same time, we want integer values only. So that really would include, or I'll say at here, both series converge at p equaling 3, or say p equaling 4. All right. So we have just a slightly different type of problem that wants us to investigate that particular next one. If we look at part C now here, we have a little bit, we're kind of raising the bar a little bit on this one. Brian, what do you think?
Yeah, absolutely. So, let's take a look here at part C. Says, I'm going to read this to you, just I want to make sure we see all the details of this question. So let p equal 4, so we are given a nice p-value. Then it says, let f of x be the function of the derivatives of all orders of x equals 2, with f of 2 equal -3, and where the nth derivative of f at 2 equals n factorial times a sub n for n greater than or equal to 1. Find p sub 3 of x, the third degree to the polynomial for f of x, centered at x2. Holy cow, that's a lot of information, right? If I'm reading that as a first-year Calc PC student, I'm thinking, okay, this is too much going on right now, right? It's a little bit confusing. We were just doing some p-series, which seemed reasonable, and all of a sudden we're talking about polynomials and derivatives and all this stuff. And so getting the skills of learning how to break these problems down, right? Tony and I would use the phrase deconstruct sometimes with our own students. Talk about when you see these problems have a lot going on. I think what happens is students get focused on the introductory information. You're trying to process, internalize all this beginning info, that first sentence of the problem. You're paying attention to the derivatives of all orders, maybe like, what does that even mean? This random f value, talking about function f, and we have some really scary looking equation for f of n. And that stuff really is not the important stuff. Whenever you have a lot of information, I really think the best place to look is at the end of the question to see what is the actual question wanting us to do, right? Ignore that beginning stuff for a minute. We're going to come back to that. But until we look at the actual question and think about what it wants, then none of that beginning stuff is going to make any sense because you don't know what that's for until you know what it wants you to do. So I always call this looking at the question in isolation. I mean, ignore all the information. There's a graph, there's a table, there's an equation, there's something written like we see here in the beginning. Ignore that and go to the question and say, okay, what does this want? Well, this problem says find p sub 3, which is a third degree Taylor polynomial. We did those last week, right? And then for f of x, that's a function that we're going to be approximating. We're going to clone that. Centered at x equals 2. So I look at just that one sentence. I think, okay, third degree Taylor polynomial means that n is 3, right? That's third degree. And then f of x is our function. And then centered at 2 means our c value is 2. So before even looking at the early information, we know how to create any third degree Taylor polynomial. Whenever I see a question talking about a polynomial or Taylor polynomial, I like to first just sort of route the generic form of what that polynomial will look like. We know that any third degree polynomial centered at some value, if we're doing it for f here, is going to be f of c, which is 2 in this case, plus f prime of c times x minus c, plus f double prime of c, x minus c squared over 2 factorial, and then f triple prime of c times, I can put a 2 there, right, for c value, x minus 2, I can put 2s for all those c's to the third power over 3 factorial. So this is our generic sort of setup of what a Taylor polynomial should look like. And we know once we have our generic setup, our job is to assemble this, right? We got to put it together. How do you assemble it? Well, like Tony mentioned, it's sort of an analogy to IKEA furniture. We give you all the pieces, you got to plug them in the right place. Well, to assemble these, we have to always calculate when you're making a Taylor or a polynomial. Your job is to plug in numbers for all those f and f prime, f double prime expressions are. We have to find out what they are. So we can create a polynomial simply by finding f prime, f double prime, and f triple prime. Plug those numbers in. We've assembled our polynomial. And now that we know we have to find those values, this initial stuff starts to make a lot more sense because it tells us, hey, if I want to find all those values, here's a formula for it. And in fact, they go ahead and tell us the first term, right? They tell us in the stem that f of 2 is -3. So we already have that one figured out. And now I got to figure out f prime, f double prime, and f triple prime. Well, we have this formula here that says, okay, if I want to find f prime, that means that n is 1. It's the first derivative, right? So if n is 1, it's going to be 1 factorial times a sub 1. Remember, we were also now given our a sub n. And we know that in this particular problem, p is going to be 4. So our a sub n is just going to be -1 to the n power over n squared. I plug in 4 for p. 4 minus 2 is 2. So if I want to figure out f prime of 2, I'm just plugging 1 in for all those n's. I get 1 factorial times a sub 1. And if I plug in 1 to my a sub n problem, we're going to get 1 factorial times -1 over 1 squared. I plugged in 1 for all those n's, which just gives me -1. And then I need to find f double prime of 2. We're just trying to find all those f values. So now we're going to plug in 2 to our formula. That's going to be 2 factorial times a sub 2 in this case, which is going to be 2 factorial. A sub 2 is going to be -1 squared, which is just 1 over 2 squared. And 2 factorial times 1 over 2 squared is just going to be 1/2. And then finally, we have to find the third derivative. We're going to be plugging in 3 for all these n values. That's going to be 3 factorial times a sub 3, which is going to be 3 factorial times, I plug in 3 into our a sub n, we get -1 over 3 squared. 3 factorial is 6. 6 over 9 reduces to 2/3, so we end up getting a -2/3. So we just calculated all those f values. Notice how when you write out the generic form of the Taylor polynomial, it really helps you know what you're supposed to find. So when you go back to the information, it wouldn't have mattered if we were given a graph of something or equation or table. This process wouldn't change. It always gives you sort of that first entry point into the FRQs. Look at the question, write down what you know about the question, and then go back and figure out how all of that information that the Calc gives you is going to help, right? Don't get focused on that information up front. So now we're ready to assemble our Taylor polynomial. One thing I love about doing these lessons with Tony is you didn't get to see us, but even though Tony and I were presenting back and forth each day, I would do one lesson and Tony would. Each of us was on live in the background watching when the other person was teaching. So I saw every single one of Tony's lessons. We planned every lesson together. Our wives, Tony gave a shout out to his wife the other day. Shout out to my wife Mary, because we had days of 3, 4 a.m. Preparing and planning these sessions together to make these as good as we can for you guys. But one of the things I've loved about Tony's lessons is I pick up so many little tricks and tips I'm going to use with my own students. And one of the things I love that he did was that analogy of an IKEA furniture. If you missed that lesson, it was last Thursday. Taylor polynomials part 2. Go back and check that out. It'll give you a good way that we can think about assembling. Now we have all our values. We can just assemble this. So we have -1 here for f. That's not right. We actually know, don't we, what f of 2 is? It was given us in the problem. It's -3. And then f prime of 2 is -1. So it becomes -1 x minus 2. And then f double prime of 2 is 1/2. So we're going to get 1/2 x minus 2 squared over 2 factorial. And then f triple prime of 3 is -2/3 x minus 2 cubed over 3 factorial. And on the AP exam, once you have a numeric answer like we have here, we're not required to reduce or simplify arithmetic once you plug values in. So you can leave your answer like this. I would probably recommend on the real exam leaving it like this, but then realizing if you need to use that answer later in part D or something, you might want to reduce it before you move on. So I'll leave that one for Tony, but if we reduce this, we're going to see what this looks like. And so when we reduce our answer, it simplifies to this right here. But I would probably have left it like I had it for part C, because what if you reduce it on the exam? And because you're going fast at the short exam, you're a little bit stressed out because it's different than what you're used to. If you make an arithmetic mistake, try to simplify and your brain just reverses 2 numbers or something silly, well, guess what? You're going to lose a point. You're not going to get that answer point because you went too far and you made a mistake. So I'll probably leave it unsimplified like I had it. And then if you need that answer for something else in part D, then that's when I would reduce it, is in part D. That way you got all your points for part C before you move on. So I would call that problem a level 4 problem. It really wasn't that difficult, right, to come up with that Taylor polynomial. But notice how the exam turned the tables on us so quickly, right? We were talking about convergence tests, and all of a sudden they did a 180 and started asking us about Taylor polynomials. So that's why it's a level 4 problem, because a student who gets a 4 or a 5 on the exam is able to make those connections between ideas. So we could go from a convergence test into a Taylor polynomial with all that information and adapt, find a way to get into the problem, and then know how to use that information to solve our problem. So part D is going to finish us out. It's going to take it even one step further and make some connections with some stuff, even from AP. So I think I'm excited to see how Tony tackles this part.
Yes, it is. It's just going to ask us to kind of move into the realm of the derivative here. So if we read this, it says use that p sub 3 of x polynomial that you found from part C, and let's find p sub 3 prime of x. And then it extends to say at or when x equals 3, the series, the summation c sub n is a p series whose first 3 terms correspond to the 3 terms that we found p prime 3 of x. We want to determine if that new series converges or diverges when x is equal to 3. So we have gone ahead and taken the answer from part C, and we have done a little bit of simplification. So you can kind of verify that for Brian's answer to this answer, that we do obtain those coefficients, particularly that 1/4 and that -1/9 there, for sure. So what we're going to do here is we think, okay, well, finding p sub 3 prime, that's going to be our first objective. And that's not going to be a very difficult thing to do. This is essentially just a polynomial, so we'll take the derivative the way that we know how. And we get, well, of course, the derivative of -3 is 0. The derivative of -1 times this x minus 1 is just going to give us a -1 at that stage. And then when we take the derivative of the next term, the 2 and the 1/4 multiply. I'm going to go ahead and reduce that on the fly if that's all right, 1/2. And then we have quantity x minus 2 here. And you know, I think is there potentially, where are we centered on this polynomial? May I ask, are we centered at an inappropriate place here? No, we're fine. No, we're fine. I'm sorry. I was looking at, I thought I had some kind of this just seemed kind of unusual here. Does that look unusual?
It always looks a little bit unusual to me.
We're centered at 2, I believe. I want to say that I should have a 2 here. Is that right?
Yes, I think we are centered at, it's supposed to be 2.
And that was in the part C stem, so I had to kind of go back and see that. So nonetheless, I still have the same derivative going. I just had an inappropriate piece of 3 there, so sorry for that confusion. And if we continue here, we take the derivative of the last term, the 3 and the 1/9 will multiply to give us,
right? Okay. Now, it's not going to be showing on the cheat sheet.
Calculus. Data polynomials. Infinite series. Differential equation. Calculus. Data polynomials. Infinite series. Differential equation.
Well, good morning, everybody. We are so excited that you are here today because today launches the very first day of our official 2020 AP Calculus BC exam review and prep. So for the next several weeks, Tony and I are going to be doing something a little bit different because in the last several weeks, you have seen Tony and I sort of going back and forth, right? We've been going back and forth with our Zoom sessions, and I've been doing Tony's been doing one day, but now we're going to be working together on these sessions live each day. Sorry, I'm a little bit distracted. Tony, are you wearing a mask right now?
Well, yeah, I mean, you know, obviously we're still amidst this COVID-19 scare, and I figured with you and I finally being together doing these lessons in the same room, I probably should take some protective measures, you know?
Yeah, Tony, we're not in the same. This is a virtual room. Like, I'm 30 miles away from you right now.
Oh, it's not a physical room. Oh, I don't. Okay,
No,
I'm sorry.
misunderstood. I wasn't. Yeah, we're not in the same place. I think you're gonna be okay, right?
Okay, we're fine.
Yeah. So despite all that, Tony and I are really excited that we're here with you today, and we're excited that we're going to be co-teaming these things. And I think hopefully each day we'll get a little bit more used to this and make these sessions really helpful. And so we want to share some little information about how these might look different than the previous ones. And so one thing that's the same is that the link to the materials, right, and underneath each video. So go on that link, and if you click on the link, it'll take you to a Dropbox, and then you're going to find the materials that we're going to be using that day. And I'll remind you guys, if you're new to these sessions, that we're writing brand new problems every single day, things that aren't in any textbooks, things that aren't on the AP exam yet, specifically designed for what we think as calculus teachers might mirror or prepare students for this year's exam. And so download that. You can follow along with the problems. And as always, each evening we'll have the typed up detailed solutions for those problems there as well. So the things that we're going to do differently. First of all, we're going to be doing some specific prep this week on just BC only topics that are on this year's exam. So this week each day is a different review unit. So today we're going to be talking about all those convergence and tandem polynomials from unit 10. Now remember, there's only 5 topics that are tested in unit 10. So we're going to be covering just those tested topics. So everything we're doing these next several weeks will be only on tested topics and then in ways that we think the exam might look like. So it'll be a BC topic each day this week, and then next week we're going to spend the whole week on connecting the AB and BC topics together. So we'll be looking at some AB stuff because even though there's no AB subscore this year, there will be still a whole bunch of AB features, right? Because it's going to be a whole comprehensive course. And so we're going to find ways to look at those AB topics for the first part of the year, and then also connect, right? It says connecting AB to BC. So for example, next Monday it's limits and continuity. So look at limits and continuity from AB, but also how can that stuff from AB be connected to a BC? How might that look in a big FRQ that we're going to see this year? So we do know that the exam this year is going to look different than in years past. We have some very unique circumstances. And so Tony, I know you've spent a lot of time looking at this exam and looking at how it's going to be different in years past. So will you walk us through how this might be different this year versus what we've seen or been accustomed to?
Certainly, as you probably have heard, the 2020 exam is going to take on a little bit of a different look, consisting of the 2 free response questions. So obviously we're anticipating that shorter test, but what sometimes we kind of might not realize, and Brian and I have tried to kind of convey this over the past few weeks, is that the makeup of those free response questions may not be the traditional kind of free response that you've seen in the past. For example, when you think about a free response question, the anatomy is a stem, which is the preliminary information that's provided, and then you get into your part A, part B, part C, etc. But what Brian and I are anticipating is the fact that you might see a lot more stems that deal with graphs, tables, numerical values in a table, and probably a little bit less emphasis on the function written analytically or algebraically, because we're anticipating the fact that the College Works going to safeguard against the use of some kind of symbolic manipulator that would allow you to gain a little bit more insight into the question than otherwise. So that's what we're looking at for these particular problems this year. If we kind of move into the bulk of today, we have a document there that you can access that does contain these items here. I'm not going to go into detail here with those 5 topics that Brian just spoke of in Unit 10, but you can use this as a nice quick stop shop, one-stop shop to kind of look through those convergence tests and the definition of the Taylor polynomial that Brian spoke about last week if you need a little bit of help with these problems. But our very first problem is this BC1 that we're going to call it, and I think, Brian, you're going to take part A here.
Yeah, so this is our first FRQ practice for this coming exam. All the problems today are designed around Unit 10, the convergence and Taylor polynomials. And what we're going to see on any good College Board FRQ is that one FRQ will tie a lot of questions together. So right now we're looking at all the things that are pretty much contained in Unit 10, but we're going to make some connections that maybe you didn't always think about as you're covering that unit. How we could have a question that starts off with convergence and ends up with Taylor polynomials or vice versa. Who knows how College Board is going to take us on one of these FRQ problems. So our very first one is going to be this BC1, and it's given us 2 different sequences. A sub n we can see as this alternating series, -1 to the n over n to the p minus 2, and then B sub n is -2 over n to the 6 minus p. And so part A, this says, okay, let's let p equal 2.5, so they're telling us a p value, and then show that both of these series, A sub n and B sub n, converge. So if we go ahead and plug in our 2.5 p, notice what we're going to get. Remember, it tells us let something equal a value. It's probably a good strategy to go ahead and write out that series or that function, whatever it is you're working with that value plugged in. So when you see it, it sort of starts to make a little bit more sense, right? And so we have for the first one, -1 to the n on top over n. If I plug in 2.5 minus 2 is just going to be 1/2, right? So that's what we get for the first series. And then the second series over here, I'm going to write this one in red. And so same idea, we're going to plug in 2.5 p, and now we get -2 over n. And if p is 2.5, 6 minus 2.5, I got to think about that for a second. That's going to be what, 3.5 there? And so it's going to be n to the 3.5 power. And the problem wants us to show that both of these series converge. So let's start with the first one in blue. Well, I noticed it's got this -1 to the n, right? So whenever you see that -1 to the n, or something that's similar or something that's equivalent to that, what we should be thinking about is our alternating series. So it is an alternating series. And so we learned that to show an alternating series converges, there's going to be 2 requirements. First of all, we have to figure out that A sub n in this case, and I know it's a little bit different than what we have here. So maybe I'm going to change that so to avoid some confusion. Instead of calling this A sub n, I'm going to call this C sub n. C sub n is just a portion of the series that's not alternating, right? So it's the 1 over n to the 1/2. So in order for an alternating series to converge, we have to ensure that the non-alternating part, which in this case is just 1 over n to the 1/2, that the limit of that as n approaches infinity should be 0. Well, it's pretty clear. If I plug infinity into the bottom, this is going to approach 0. That fits the first requirement. But remember, for an alternating series, we have to also show that 1/3, and we have x minus 2 squared. Now notice along the way, I really didn't have to worry too much about a chain rule that produced any extra factors because the derivative of what was inside was x minus 2. All right, well, what are we trying to do here? Well, we are told that this new summation, this new series, n equal 1 to infinity of c sub n, is really capturing the essence, let's say, of this brand new polynomial
polynomial that we found, at least the first few terms of it. But if we stay true to the nature of an infinite series, then we know that we're continuing on into infinity. But we are then now becoming very concerned about what's happening at x equals 3. So what I can do at this stage is we can physically let that x value become 3. And as I do that, we will replace every x that we see with 3. Let's maybe simplify on the fly here. So 1/2 quantity 3 minus 2 would be, of course, positive 1/2. Subtract 1/3 quantity 3 minus 2 squared would be minus 1/3. That's really all that we have to go by. We can maybe predict what some of the next terms are going to be, but I don't think it's really going to be important because our task is to determine whether or not this brand new series that we just started to write is going to converge or diverge. And if we take a little bit of a closer look at this, we see that, oh, well, this definitely is an alternating series. It has that behavior from the very initial stages, and the fact that it is behaving very much like our P series that has the exponent of 1, which we call the harmonic series. Put those two ideas together, we have the alternating harmonic series. Now, albeit maybe the signs are alternating a little bit differently than the alternating harmonic series that we saw a few days ago, but nonetheless, it's still an alternating harmonic. And because of that, we can say this series will converge. And if we want to give a little bit more justification, we can just simply say because it is an alternating harmonic series. And I believe the sum of it would be, I think, negative natural log of 2. Remember, Brian talked about the alternating harmonic series where the first term is positive would become natural log of 2. Now, that is something that you will not need to know on the AP exam. So I think that wraps up our first question. If we kind of start to move into our next question here.
Well, Tony, before you do that, I'm going to interrupt you because I feel like we deserve some kind of reward. Right? We got through our first FRQ, right? Our first practice FRQ for this Unit 10 review. And so I think everyone deserves a reward for getting through that. And I think our reward should be some adorable puppies. I don't know. I was feeling the love for some puppies this morning. So I found this picture of puppies. And of course, if my wife and kids see, I'm sure we'll have another pet in our house, much to my disapproval. But I have to give some love out to some adorable puppies because who doesn't love some puppies now? Now that I'm showing this, I'm starting to think a little bit. I know last week you mentioned how Wimpy, your lovable dog Wimpy, was a little bit jealous of my dog Buddy getting some airtime. We talked about Polynomials right on Wednesday. And so you had to bring him in on Thursday. So I'm hoping that our dogs don't see this. I know that sometimes my dog and your dog both like to watch these videos and follow along with us. But hopefully they don't see this. I know that my dog is jealous. I don't know about you. Is Wimpy a jealous dog? Is he going to be upset about this?
I tell you, Wimpy is a little jealous, and I want to tell you, I'm going to share something with you here. I just received this morning, and I was shocked. But what we have right here, ladies and gentlemen, Brian and I have celebrity Calc dogs. They have their own Twitter account, and there you see Wimpy on the left, Buddy on the right. And we just received this tweet from them saying that either we get more airtime on your next broadcast or your home office is next. Celebrity dogs rise. So there you go.
I think our dogs are getting a little bit ahead of themselves. They seem like they are pretty much in charge of our world. They think that they're pretty much the top dogs, I think. But I'm going to look like your couch. So I'm okay with it right now that it was your couch that was torn out and not mine. But I'm glad it wasn't mine. But so let's jump into BC2. And next time, maybe we'll be a little bit more careful of what rewards we show. Maybe we'll have to show some rewards of our own dogs in their amazing cuteness instead of showing some puppies, right? So BC2 is another really cool problem. So now we're given a series of a sub n, and we're defining a sub n as this function here of a 5 times x plus 3 to the n all over negative 6 quantity to the n power. And we're going to determine if this series converges or diverges when x is 1. So it's really similar to what we saw on question 1. They give you an x value and ask you to do something. So let's just go ahead and plug in x equals 1 and see what we get. So we take the series from 0 to infinity. If x is 1 in this problem, then 1 plus 3 is just going to be 4 to the n. And notice both the numerator and denominator here have a part of it where it's to the n power. And so we could use some nice little properties of arithmetic and write that as just 4 over negative 6 all to the n power, which can reduce to negative 2/3 to the n power. So really when x is 1, this whole expression reduces to 5 times negative 2/3 to the n power. And I don't know if you remember this or not, but this looks a lot like geometric, right? So when you have these series, I think a really good strategy when we talk about convergence and divergence is thinking about where are the n's, right? And the problem we talked about that, we did convergence last week. If n is the base of expressions, it's the base that we saw in the last examples. Those are examples of P series typically. And then if n is the exponent, like we see here, that's going to be an example of geometric. And so you see these problems always look for the n, where the variable n is at, because that gives you a really good insight into what type of series you're working with, which will hopefully trigger in your memory what requirements there are. And so this is a geometric series where the r value in this case is negative 2/3. And now that we know that it's a geometric series where r is negative 2/3, we have a rule, right, for geometric series that says the absolute value of r needs to be less than 1. Well, guess what? The absolute value of negative 2/3 is just 2/3, and that in fact is less than 1. So this does meet the requirement. So this will converge by the geometric series test where r is less than 1. So again, a pretty straightforward question, kind of a level 3 type problem. So nothing super difficult there. But like we saw before, we're going to see a little bit more complexity as we go on. I think, Tony, you got a really neat way of walking us through something like part B, where it's a little bit more abstract and asking us to use our understanding of series, but kind of that reverse way.
Yeah, let's take a look at that. I'll share what I got. Now, what I've done here, I kind of started to cheat a little bit. I started to write that summation expression, just kind of reordering some things. I noticed that this x plus 3 is raised to the n and this negative 6 is raised to the n. So I got that brand new version of this series here. And then what we're supposed to do here is we're going to allow that this series is going to be equivalent to L. So it has a finite sum of L. L is a real number. We want to show that there is a value of x that essentially will make that happen. And since we've already established the fact that this is indeed a geometric series, we can use the idea that the sum of an infinite geometric series is built so that you can take the first term, which that would be, well, let's let n equal 0. We find out this x plus 3 over negative 6 to the 0 becomes 1. And then we have 5 times that 1. So our first term is certainly going to be 5. And if we look at the r value, now this is an r value that's very sort of disguised, let's say. We don't specifically know what the x is, which means this is kind of like a power series to an extent. So we have this r that's going to be x plus 3 over negative 6 that we'll subtract from that 1. Now we just do a little bit of manipulation with this and simplify. And let's see, algebra. What do we have here? Let's see, we have 2 negatives here that will become a plus. How about I get a common denominator of 6? That seems like that could be a good idea here. So I have that new denominator, and we can simplify even further, it looks like, and have a 5 on top over x plus 9 all over 6. And if I multiply by the reciprocal, I can simplify even further to have something along this line. Now we have to remember, what did the part B say that this is going to become? Well, this series was going to add to 15. So I know I can link that to the number 15. And at this point, we can probably solve this equation fairly easily. So if we cross multiply here and divide over our 15, we see that x would be negative 7 in this case. All right, well, okay, if we put this all back together, really, what is this saying to us? Well, it says here, now where x is negative 7, what we have going on here is that this series, the summation as n goes from 0 to infinity of our friend a sub n, which consists of 5 times, now negative 7 gets a chance to plug himself in for this x. So negative 7 plus 4 is going to, or plus 3 is negative 4, I should say, to the nth power, all over negative 6 to the nth power. And if we just do a little bit of simplifying here, we could rewrite this so that it looks much more geometric in nature, right? We could consolidate the bases that have a power n, maybe all the while reduce a bit. And so I have 5 times 2/3 all to the n power, which we can certainly see is a convergent geometric series.
Tony, I love this problem because they can maybe rephrase this. Like, students thinking about how else my college board twist this. Instead of saying show there is a value, they could maybe have asked show there is not a value, right? Because when we got x equals 7 here, we really found an answer, but we haven't shown there's a value until we know that series converges. So we got to make sure when you plug it back in that the r value was, like you mentioned, a convergent r value. So they might ask something a little bit different, because they might say show there's not one. And what would happen? What would that look like? What would the final answer be that you would show if it doesn't have a value of a specific x value?
Oh, it's very possible. I would say that it potentially could produce an r that would not be within a realm, maybe an r that's larger than 1. So yeah, it's a very good take on that. All right. right, part C, I believe, is that me? I believe that very well might be me, right? Part C says the d sub n is going to come into the horizon here, and it's defined as a sub n over n plus 1. We want to find the interval of convergence for this summation. Now, what we're going to have to do here is, because we certainly have a much more robust function, or series, I should say, on our hands, because we're going to kind of consolidate. We're going to marry this a sub n expression with this new d sub n expression just a bit. And so we have something that looks like this. The series from n goes from 0 to infinity of 5 quantity x plus 3 to the n over negative 6 quantity here to the nth power. And then what a great time to put our n plus 1 here in that same denominator. So we have now obtained a slightly more complicated function, or series, I should say, that I don't think that we can necessarily classify as geometric. So when we have more difficult series to contend with, and if we're asked to find convergence, we use our great friend, the ratio test, which we know is going to be a tested item on the exam. So let's jump right to that. We're going to use the ratio test. And if you recall, the ratio test says that we are going to, first of all, analyze the limits as n approaches infinity of the absolute value of the a sub n plus 1, or how about I say d sub n plus 1 expression over the d sub n expression here. And specifically to this problem, that will give us, reading through this, swapping out those n's with n plus 1s very carefully each time we see it. And then instead of dividing by the original d sub n, I'm going to elect to multiply by its reciprocal here. Saves just a little bit of time in the calculation. And what do we have on bottom here? 5 times the quantity x plus 3 to the nth power. And now let the simplification games begin. So after I write this limit statement, we're going to start to see what happens here. And one of the things that I see that happens right off the bat is, oh, some 5s will cancel away. That's wonderful. As far as these negative 6 to the n over negative 6 to the n plus 1 is concerned, I am going to have a negative 6 to the first hanging around in that denominator, it looks like, just for a while. So we have those taken care of. How about the x plus 3 to the n plus 1 over x plus 3 to the n? That would give us x plus 3 to the first power in the numerator. And it looks like I've got, I've got an n plus 1 over an n plus 2 that, quite frankly, I can't really do much about. They're going to have to stay in this mix here for just a while. But that's okay, because we know how to deal with that. So what we're going to do at this point, and students and teachers can handle this in different ways. One of the things that I like to do is maybe isolate the piece of this expression that contains the n values. And so I'll write those together in their own separate limits, let's say. And then I know that I can split apart this limit of product by multiplying the two separate limits together under these conditions here. And I also notice that, well, I've got the absolute value of x plus 3 over negative 6. Really, when it comes down to it, that negative 6 can change to a positive 6 because of the fact that the absolute values are going to have a major effect on him. And if we separate those, and what we know here about this limit is that we get a 1. Okay? Now, this other limit, we can let n approach infinity all day long. That's not going to be a problem. And in doing so, we're going to get just the absolute value of x minus 3. I'll tell you what, I'm going to just write that 6 in the denominator without worrying about absolute values at this point. So what I know is, in order to converge, right? I'm going to go ahead and add that right here. In order to converge, the conclusion of the ratio test says that this result has to be strictly less than 1. So that's going to force me to go ahead and take this a little bit farther and find this interval of convergence. So I'm going to go ahead and multiply over a 6. And then to solve this absolute value inequality, we can go ahead and set it up as a compound.
Should that be an x plus 3 on that one, Tony?
Oh, it probably should. I think this should be a plus. And I'm going to take this guy here as a plus and that a plus. And that worked. Definitely thrown off our answer. Thanks for that. And then if we finish up, we have negative 9 less than x is less than 3 in this case. All right, now our job isn't done. Unfortunately, we have just a little bit more fish to fry here because we don't really know what's happening at these two endpoints. And that's one of the things that we emphasize quite a bit in our ratio test lesson, in our convergence of series lesson, our interval of convergence lesson, in that we have to check these endpoints. Doesn't matter which order you check them. So if we check the left one first, the negative 9, what we are essentially doing is going back up here to this blue series and just saying, hey, what are we looking at if we let that x value be negative 9? And it turns out that we have 5 times negative 6 to the nth power over negative 6 to the nth power times n plus 1. And once all the dust settles and you see that these negative 6 to the n's cancel, you have a nice 5 over n plus 1, which, whoa, that's kind of familiar. That is definitely a divergent harmonic series on our hands. So we are not going to have the luxury of converging at that left endpoint, unfortunately. So let's go ahead and just briefly check the right endpoint. Doing a very similar process here. We're checking the positive 3, and the series is going to be n equals 0 to infinity. I might scroll up here as I put a positive 3 in here. I get 5 times positive 6 to the nth power over negative 6 to the nth power times our negative 6 to the nth power times our n plus 1. And what's going to happen here is that we're going to retain the alternating component. These two guys are going to essentially reduce to negative 1 to the nth power. So now we have the alternating harmonic. Or you could say, hey, really what we've got is an alternating series that if we perform the steps, we can see that this will indeed converge. And maybe your best reasoning would be by the alternating series test. And then the last thing to do, throw this all together by adjusting your inequality. And maybe it might be a little bit easier, especially if you're using a text or a typing entry type of interface for your AP exam this year. We could write this in interval notation instead of inequality notation, which means we will not include the negative 9, but we will include the positive 3. And that takes care of part C there.
That's awesome. So as you've seen, these problems are getting more complex as we go, right? So Tony and I are writing these problems so that way you can see it sort of at the beginning, like the level 3 questions, level 4 maybe at the end, level 5 stuff. Doesn't mean the AP exam is going to be that way. It doesn't always mean the questions are going to get always harder as you go on. So if you take an actual AP exam, if part A seems really tough, don't be discouraged and think, oh my gosh, I can't do part A. It's only going to get harder. That isn't how the exams are structured to be guaranteed to get more difficult as you go. We're just doing that on our problems typically right now because we want you to see how these problems might evolve, how we can have a certain stem, and how you might ask some more intro type questions, some more depth of knowledge questions, and then some really good challenging questions. So really briefly, I want to walk us through part D just for a minute. This is the last problem we get through today. But don't forget on those files, when you download them, you're going to have 2 more complete FRQs that you can work with beyond just these first couple that we've done. So you can do those. The typed up solutions will be in there as well. And then you go on that Dropbox link, there's always another folder that says supplementary videos. It's been empty. But what we're going to have tonight for you or today is for the third question, BC3, I'm going to make a short video since I'm not going to get to it at the live session. I'm going to make a short video today to walk you through that on top of just seeing the solutions, kind of walking. So there's some really important ideas there that I want to make sure you see beyond just the typed up solution. So check out that little folder for supplementary videos and you'll see a link to a special video just for BC3 on here. So this is part D. I went ahead and copied over what Tony had from before. And it says, okay, the first 3 terms of the series D sub n that we talked about in part C become a second degree Taylor polynomial for f(x) centered at x equals -3. Find f double prime of -3. So I took the liberty of taking that series that Tony gave us and then headed and writing out the first 3 terms because the first 3 terms I'm plugging in 0 for n and then 1 and then 2. And we come up with this right here. And we can sort of see how that could be a Taylor polynomial, right? Because we see these x plus 3, and it would be centered at x equals -3. And we're going to see this problem. I think it's important enough to spend 10 seconds here looking at it because just like before, we have some confusion. It says find f double prime of -3. Well, how do we do that? Well, we know there's a second degree polynomial for f centered at x equals -3. And so what if I went ahead and wrote out what would a second degree polynomial for f look like? Again, ignoring the beginning information. If we were trying to make a second degree polynomial for f, it would just have been f of -3, right? Plus f prime of -3 times x plus 3 plus f double prime of -3 x plus 3 squared over 2 factorial. This is how we would build it, right? And if we build it, we realize, oh, this question wants me to find f double prime of -3. So I don't need to build the whole thing, but I know that this f double prime of -3 is part of this x plus 3 squared term, right? That this term, this whole entire term, is going to match up with that term. So I know that f double prime of -3 times x plus 3 squared over 2 is going to be equal to whatever we got here, the 5 times times x plus 3 squared over 36 times 3. I didn't multiply that out because I don't want to make a mistake on that. These two things should be equivalent if it's a polynomial. So I can sort of cancel out the x plus 3's, which gives me f double prime of negative 3 over 2 equals 5 over 36 times 3. And if I want to find f double prime of negative 3, all I have to do is multiply both sides by that 2 to get rid of it. And f double prime of 3 is going to be 5 times 2 over 36 times 3. Remember on an AP exam on first response question, we're not required to simplify or reduce. You don't have a calculator nearby, so you can type it in a calculator if you want to, but I would probably leave it like that. And there's our solution. So the problem that we did not get to today is this third problem. I hope that you'll spend some time doing this problem because it has a table and it has a really good flow to it, where it starts off kind of basic and it kind of builds and builds and has some really neat components. So like I said, look in that other folder because we are going to see a supplementary video there today where I'll walk through the individual pieces of that. So we want to end on that part today. Don't forget tomorrow is going to be day 2 of exam review with dealing with different integration formulas. And as always, we like to get tweets from you guys. And so tell me what we have on tap today for our future tweets.
We got some great things. AP teachers rock. We got Mr. Huckabee. My AP Calc teacher for 2 years now is such a wonderful teacher and a caring individual. We always made our lessons and days in his calc room fun and worthwhile. We love teachers like Mr. Huckabee, that is for sure. And as far as our AP students rock, so proud of the BC Calc students at Old Day West. Zoom meeting each day, never complaining, showing great character during these times. It is an honor to be your teacher. I know your teacher, Mr. Patrick Flynn, does a great job. And I think Brian, you probably done a little bit of work. I think in the Old Day outside of Kansas City.
Some of our AP workshop for our teachers. They're great teachers out there.
Yes, that's definitely for sure. And once again, if you do have some technical glitches, we would like for you or your friends to reach out to cb.org/tech so that they can take care of any of the problems that you're having, give you the devices that you might need, the internet service that you do need as well. And wow, we thank you for watching. It's been fun. Ryan, it's been everything that I dreamed of and more. Great job today. Great job. And I look forward to tomorrow when we're talking about what PC integration techniques, I believe, right?
Yeah, absolutely. And Tony, I have a challenge for you real quick tomorrow. I want you to think of your favorite TV show or favorite movie. Don't tell me what it is, and then get something in your background. Make your background something that's not directly the movie, but something that would be a hint toward the movie tomorrow morning. I want to see if the viewers and myself, if we can guess what your favorite movie or TV show is based on the hint that might be behind you. That's our good idea.
I love it. I think that would be a great idea. That would be a great idea.
Awesome.
All right, well, we're out today. We want to thank you for watching on behalf of Brian and I. We will certainly see you tomorrow. We want you to stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
In the midst of solving this integration question. So what that means is this antiderivative from 0 to 3, the area under the curve from 0 to 3 is just 5, and hence our answer becomes 5 over 2. Okay, big fan of the problem. I really like a lot of the things that it brings to the table. Now, if we take a look at part C with this question, and I'm going to scroll down here just a little bit, we see that we have another sort of amalgamation of a lot of different ideas in that integrand. Finding the integration from 0 to pi over 2 of cosine of x times f prime of sine of x. So again, we want to start from the basics and think, okay, can we pull this off with a u substitution? If we play our cards right, is that going to give us the semblance that we want? And if it doesn't, then we can move on to a more advanced technique. As we look into this a little bit further, we have this sort of adage that says sometimes if you let u be some value that's located in parentheses, it typically will get the job done for you. So I see sine of x that's located in parentheses. So if I allow that substitution to take place and I take its derivative, we are going to be quite pleased with the result. The derivative of sine is positive cosine of x, and we'll put our differential dx on the other side, and we say, oh, we have that perfect match that we dreamt of. So really what we got here is just the integration of f prime of u with respect to u. Okay? Now, we could, of course, change the boundary 0 to pi over 2 to become u's, just like we talked about before. But let's say that you're opposed to that. Let's say you're not really into that in this particular part of the problem. What you could do is back substitute. In other words, you could take that u value, that sine of x, and throw it back into its position. Okay? And if that is the case, then we could say, let me make sure that what do you say we integrate this first, and then I'll do that. So if we integrate the f prime, we're going to get f, right? And then we'll back substitute that u. Okay? I'm all set to take this integral, so I don't need to do anything else with that. Now, the issue here is that this boundary can now retain its original sort of appearance, and those two boundaries, pi over 2 and 0. Now, the only thing I have issue with this thing that I've written on the screen is that it's not really a legitimate. It could stand maybe a linkage error. So maybe I put some temporary placeholders here. Maybe I put a b there, maybe an a there, just to say that certainly there are going to be some definite intervals. And at this point, I think we can just go ahead and evaluate this. So if I run my pi over 2 in for x, I have the sine of pi over 2, which of course we know to be 1. And then I'll subtract, and then let's run our 0 in for x. And of course, the sine of 0 is going to be 0. And then we hope we could glean some information from that hideous mess that I have up on top of the screen there. And we see f of 1. Well, this is a graph of f of x, so that's good. And f of 1, yep, we can just barely see it to the left of the spill. It has a y value of 2. And then we can do the same thing for f of 0. We see that it's right here nicely on the y-axis. And it has a value of 3. So when you put those two guys together, you're going to get a -1 for the final result. So that takes care of that part C with problem 1. And I think we're going to go ahead and turn it back to Brian. Brian's going to move into another BC technique here with part D.
Yeah, before we jump into part D, because these are recorded, I know you guys can kind of rewind and fast forward, but I want to make sure you saw the nuance there of part B and C, because they seem like there's just two U sub problems, right? Why do we do two U sub problems in a row? But I hope we recognize that's what we did those. If you didn't catch this, go back and look at it. They're both integration. They both required U sub. One of them on part B, we applied the fundamental theorem of calculus, right? Or on part C, we actually integrated because after we did U sub on part C, it was the integral of f prime. But on part B with U sub, it became the integral of f. And so since we're given a graph of f, we didn't actually use the fundamental theorem. We didn't actually integrate f on part B. We just connected the idea that the integral of f is the connection to the area under the graph of f. But in part C, we couldn't make that same connection because we didn't have a graph of f prime. So Tony had to U sub, go ahead and do that fundamental theorem where he integrated f prime, and then the fundamental theorem calculus to evaluate that. So making those connections between sometimes when we integrate a function, we can connect it to the area under curve, and sometimes when we integrate a function, we have to use the fundamental theorem of calculus. And so they both required U sub, but once we did that, they had very different divergent strategies to solving them. So if you didn't make that connection, go back and look at those because they're very similar problems, but had different endings in terms of how we would work them out. So we're gonna go back at part D. And before I do part D, just quick, I want to quick guess. Is your TV show something from this old TGIF, like those Friday evening lineups that they used to show with like Full House and stuff like that?
Certainly, as this debuted with the Friday time slot. I think eventually got moved to Tuesday, but that's where it all began.
Okay, so I think I'm onto it. Like, I'm blanking right now on the name of it. So I almost want to just let you take over the rest of these problems so I can think about this problem, but I can't think and do math at the same time. It's not. Is it Family Matters? No, that's not it. That was Urkel, wasn't it?
That was Urkel. You're very close.
Okay,
okay. Production. You're very close.
All right, I'm gonna come up with this. So I need someone to text me the answer. I'll slide it down my phone so Tony will think I remember this because I gotta get this. So the last part of this, I'm gonna go through this a little bit quickly because it's more about notation than it is anything else. And you can rewind this if you need to and kind of refresh what we did here if you were kind of missed a part of this. But there's so many good problems in this lesson that I'm probably gonna be able to expose today and kind of work through with you. So on part D, it says it's known that the integral from infinity is equal to 9. So this is one of those problems where instead of saying find something, A, B, and C said find the integral, find the integral, find the integral. Now I'm telling you the integral, and we're gonna find the value of A. So we worked frontwards on the first three parts, and now we're gonna have to use our same understanding but work backwards, right? But the beginning, all that's still the same. It's just what we're missing is a little bit different. So we don't know quite how the problem's going to work out. Just start breaking it down and figuring out what you do know. And so we know that the integral from 3 to infinity, but when we see an infinity sign in a limit, that's a really good indication that we're dealing with improper integration, right? Because when we evaluate integrals, the fundamental theorem, we need to have a real number up on the limit. We can't have infinity, so we have to use some proper notation and communication. And don't forget, this is a free response problem, and so it's not just about the answer, it's about your work and how you communicate your work. Not just that you communicate clearly what you're thinking and what you're doing, but that your notation, the symbols you use, are actually correct. Proper. That's why Part C, Tony went back to that middle step and put an A and a B on those limits, because if they weren't on there, he still arrived at the same answer. But technically, he would have what we call a linkage error. He used those equal signs to say these integrals are equivalent, equal to each other. If he didn't have the A and the B on that integration problem, those things would not have been equivalent, right? So even though I understood what he was thinking, it would cause an error in terms of connecting two statements that aren't the same, and he would have had most likely some kind of not earning full points in that problem, or some kind of penalty for that. And so we want to be careful that we not just do the problems, not just show our work, but use proper notation so we can get all the points that we deserve. And so here we're integrating from 3 to infinity, and so we're starting here at 3, and we're going all the way to infinity, right? Remember, that's where this other part comes in. And we know this function equals 4 over x minus a squared. So we don't really know what this looks like, so we don't know what a is. So I know there's something going on, right? That this function is going to keep going all the way to infinity. And so we want to find the total area all the way for 3 forever. And we know the total area all the way forever is going to equal 9. But I also know from earlier that the integral from 3 to 4, this piece right here, Tony showed us this was equal to 3 using our information here, right? We flip those limits and make the answer the opposite, so that's going to be 3. And then from 4 to 5, this is just a trapezoid. What I love about using area geometrically is it's okay if there's a hole in the graph, because that's not going to affect the area. We can still integrate area from 4 to 5. We couldn't take the derivative with that hole in. We could certainly do area under a curve problem. So that's a trapezoid, and you have to trust me on this, but the area of that trapezoid is 4. You can confirm for yourself if you need to pause and kind of calculate that and refresh your trapezoid formula. So I know the area from 3 to 5 is 7. That's this whole entire area right here. And that means if the whole thing is 9, the remaining part, which I'm going to sort of highlight here in red, all the way to infinity, has to be a total of 2, doesn't it? Because it has to combine to 9. So really, the integral from 5 to infinity of f of x dx is going to be 2. How am I going to solve for a? Well, we know that f of x from 5 to infinity is this function right here. That the integral from 5 to infinity of 4 over x minus a squared dx. I just replace f of x. That needs to equal 2. Now I want to find out what a is. Which value of a would give me an answer of 2? Well, luckily, we don't have to guess and check. What we're going to do is basically pretend like the 2 is not there. Let's just say we're going to integrate this. And so when we integrate this, we're going to have to use some proper notation, because we can't really do the fundamental theorem of calculus with infinity signs. So this is where that notation becomes really important. And we do improper integrals. We're going to replace that infinity sign with a variable. I like to use b for the top and a for the bottom, depending on which one you're getting rid of. It doesn't matter as long as you use some variable for there. So the limit as b goes to infinity of the integral from 5 to b of 4 over x minus a squared dx. And so this is the notation and communication we're talking about. And what's going to be important is, in order to get all of your points, remember, we have this limit every step of the way. And we're going to evaluate this limit at the very, very end. So b is some real number. So now we can use the fundamental theorem of calculus. So we're going to integrate this. We're going to plug in the limits. This limit of b goes to infinity is going to be in front every step of the way. And once we solve the entire problem, then at the very end, we're going to find out what happens as b approaches infinity. So if we're integrating this, I'm going to go to the next line here. We have the limit as b goes to infinity. And then I'm going to do some quick integration here. If you integrate this, I would probably bring this x minus a to the numerator. If you think of it like this, that we don't make any mistakes. We can do u sub, but the derivative du of this is just going to be 1, right? Because a is a constant. And so we don't really have to use u sub. The integral of this is just going to be 4x minus a to the negative 1 over negative 1 using our integration techniques. And so that's going to end up giving me, if I resimplify that, negative 4 over just x minus a. And we need to evaluate this from 5 to b. Notice I still have that limit in front, because that's the very last thing we're going to do is evaluate this limit. We want to go ahead and do the entire fundamental theorem of calculus, which includes integrating and plugging limits. So we're going to have negative 4 over b minus a, and then minus negative 4 over 5 minus a. Now the minus negative 4 just becomes a plus, right? So now we've done the fundamental theorem, and now I can apply this limit. So we're going to plug in infinity for b. So we're going to get negative 4 over infinity. Well, any real number over infinity is just going to be 0, isn't it? Plus 4 over 5 minus a. And so the integral from 5 to infinity is just going to be 4 over 5 minus a. And remember, we've already mentioned that we need that value to equal 2, because we told the definite interval is 2. Now that 2 comes into play. So this is now just an algebra problem. I can sort of cross multiply or multiply by the denominator. I'm going to get 4 equals 10 minus 2a. And then a little bit of math here is going to end up giving me a equals 3. Boom. How about that? A really nice example of improper integration using some of our old integration techniques. But really make sure you focus on those limit properties, and make sure you use a proper notation on the exam to get all those points that you want so badly. So we're going to jump ahead now to another type of problem that the one we just was very graphical stem. And then Tony's going to show us a kind of neat situation that uses a couple of how we see ideas, but more from an algebraic standpoint. So how can we see an equation problem, Tony, where it's not going to have an advantage of using calculators or textbooks or things like that?
Certainly, and this is one of the ones that could be somewhat of a challenge, I think, to write. Brian did a really good job with the initial idea with this one to provide these two factored pieces in the denominator to make this happen. So what we're going to see here is we're going to be given a function g of x that's defined as h of x over x plus c times x minus c, and we know that c is a constant of negative value. So our directive here is to find the definite interval from the lower boundary 4c to the upper boundary 7c of g of x with respect to x, and we're told that the h of x function is 6c. So we got to do a little bit of assembly here. So we're going to put our furniture pieces together, and we have our integration from 4c to 7c. And this g of x function, let's just be really specific about it. We know that it's going to have this h of x numerator that's now defined as 6c, and we have this denominator that consists of these two factors. And then we just have to sit back and think, well, what integration technique will apply here? And so if you kind of go through the cadre of techniques, it doesn't seem that this is going to follow your typical u substitution. It seems like it's got just a little bit more complexity for it to be integration by parts. And hopefully you recall this idea of partial fraction decomposition. The fact that we have a denominator, it's already factored for us, so that's a big clue as well. That consists of the two pieces, the two linear pieces I might want to have. So we probably can do that this is going to be partial fraction decomp, which is the first time that we've seen that today. So just a little bit of a kind of a blast from maybe a pre-calculus classes when you were first introduced to this. So we're going to kind of leave the calculus for just a moment and focus on just the algebra. So if we have that expression and we set that up as the sum of two distinct linear fractions with linear denominators, I want to say, we might have something that looks like this. Now we want to remember the way that you set this up is that if you have linear denominators, which is what we know we're going to have on the AP exam, then we have only constants to worry about in the numerator. All right, well, from here we can go ahead and multiply through by the common denominator, and that's going to give us just the 6c on the left side. On the right side, this a is going to be paired up with the x minus c, while the b is going to be paired up with the x plus 2c. And then at this point, our goal is to figure out what is the value of capital A and capital B, and then we can reintroduce those into that previous set that I wrote in purple. One way to do this, there's a couple of different ways, but one way that works, it's called the Heaviside method, named after the mathematician Oliver Heaviside, where you would just pick a very opportunistic x value. Let's say that we let x equal c. I like that idea because it's going to eliminate all of this expression here. In that case, all that's left is 6c on the left side, and then on the right side we have b times, well, we have c plus 2c, which is 3c. And then once we solve that for b, we discover that, hey, b is just equal to 2. That's not too bad. Let's pull off something very similarly with this other expression. Maybe let's let x equal, and here you really have the whole gamut. You can pretty much use about any x value that you want, as long as you did not make a mistake and b is indeed 2. But if you want to kind of retain the Heaviside method flavor, you'll pick something that's going to allow this expression here to equal 0. You can basically set that equal to 0 and solve for x. And we can see that negative 2c is going to be a very opportunistic x value to use, because we would see that once once again, 6c would be on the left side. And then on the right side, I have a times, well, let's see, what's negative 2c minus c? That's negative 3c. And just to reiterate, this here is going to completely disappear because it's going to have a b times a 0. And now we see that a is indeed negative 2. We got our a and b value. Now we're in business. Now what we can do is we can revisit that original interval, this one that has the lower boundary of 4c, the upper boundary of 2c, and we can assemble it using this step right here in our newfound a's and b's. Now, with your permission, I hope that you all are okay with this. I'm going to flip the order. I'm going to write the b over c, b over x minus c first. So remember, my b is 2. And then I notice that my a is negative 2. So what that allows me to do is just to subtract. And then I have that 2 over x plus 2c. And that just gives me a little cleaner integrator. I don't have a negative leading things off. It's perfectly acceptable if those were switched. You just don't want to mix up your a's and b's, of course. And now we have really a little bit easier integration problem to tackle. You will use a u substitution to an extent, but I hope that we all realize that you just have these linear factors in the denominator with now constants in the top, which is going to lead itself into being a natural log setup. So the integration of 2 over x minus c would be 2 times the natural log of, and by definition, we want to say absolute value of x minus c. Now, I think it's possible in this case. I think we said in the stem of the problem that c was going to be negative, so it's probably likely that x minus c is positive, and we could do away with the absolute values. But don't overthink that. If you want to put the absolute values and keep them in there, it's not going to be incorrect as far as mathematics is concerned. We're going to do the same thing over here. We have x plus 2c in the denominator. Remember, 2c is kind of treated as a constant. So when we take its antiderivative, we would get 2 times the natural log of the absolute value of x plus 2c. That x plus 2c, I believe, could run the risk of being negative, so I want to keep it at the absolute values. And then, of course, we have our boundaries, 7c and down to 4c. So in this particular instance, what we're going to have is plug in 7c and 4c. So you know what? I'm going to kind of alter this a little bit. I have an idea here. I see that we have 2 natural log expressions joined by a subtraction. What do you say we do this? What do you say we consolidate these via division? Honestly, I think that could make our job just a little bit easier in terms of evaluating this. It's by no means a necessity, but it can give you guys just a little bit less of a headache, I think, when you're figuring out this final result. So now let's see what we've got. 2 times the natural log. If we replace x with 7c, we have 7c minus 6c. That's 7c minus c, which is 6c. And then in the denominator, it's 7c plus 2c, which is 9c. And then we'll subtract 2 times the natural log of the absolute value. Now let's plug in 4c, subtract c, that's 3c. Boy, a lot of c's in the problem. 4c and 2c is here 6c. And we are allowed to cancel these c's because it is a non-zero constant. So we end up getting 2 times the natural log of 2/3. I guess we don't really need the absolute values around 2/3 if you so choose. And then over here we have 2 times the natural log of 1/2. And I'm going to stop the problem there. There's various ways that you can consolidate these. It's not really important. As long as you produce a numerical version of your answer that's equivalent, you would receive full credit. So I tell you what, I think if we look at part B, we see a lot of similarities. We're integrating g of x once again, and we have the same stem. So we could probably borrow some work that we just implemented from our part A and not have to reinvent the wheel. So basically what I'm saying here is that we've got a situation where this isn't a proper interval. And Brian did a good job of showing us this wonderful setup where you can let that upper boundary be, let's say, a b, and let b approach infinity. Because definite integrals, they just don't like infinity to hang around in one of the boundaries. It kind of circumvents a lot of the essence of the fundamental theorem of calculus. So it's, in essence, what we're doing is we're really looking at this problem. But like I said, we've done the heavy lifting here. So there's no need to recreate all of that work if we've already done it. So we're basically going to import an answer from part A. And that answer would still have this limit as b approaches infinity. And if you've been following along, you've got your part A work. Do you remember that step right after I consolidated those 2 logarithms into one expression? It looks something like this, I believe. All right, the only difference now is that I'm going to use my boundaries b down to 1 minus 2c. And as I input these, my limit is still out in front, waiting ever so patiently. And then I have 2 times the natural log of absolute value of b minus c over b plus 2c. And I'll subtract 2 times the natural log of the absolute value. And then here I have 1 minus 2c minus 2c, which I believe is 1 minus 3c if I'm not mistaken. And then in the denominator here, 1 minus 2c plus 2c is just going to be, that's just a 1. And then I can let my limit do its work. And I notice that in this first limit here, if you let b sort of act as your independent variable, I could let both of these b's grow to infinity. Well, you don't want to think, oh, infinity over infinity, that doesn't make any sense. We don't want to have to use L'Hopital's rule if we don't want to. But what we can remember is that if we have the degrees of our independent variables of the same order, they're both to the first degree. Remember, c is kind of behaving like a constant here. We know that the limit as b approaches infinity is just going to be 1. Well, that means all of this limit here is 1, but we still have this natural log that we're invoking into this process. So we have 2 times the natural log of 1 is 0. Okay, there's a little bit more to that explanation of how you produce that 0 symbolically, but if a student were to recognize that, that would be perfectly acceptable. And then I have my minus, and then really there's nothing else to do but to rewrite this expression, and perhaps do away with the 1 denominator because he's not really needed. And at that point, we probably could do away with the 0 altogether. And you could write the piece that's inside the absolute value a variety of ways. By no means do you have to lead off with a positive, but because we have absolute values, we could switch the order of 3c and 1 if we wanted to, but it's not necessary. Brian, where do you want to take us next?
Sure. I think on that last part there, we call that problem the Brian High School report card problem because all those B's and C's is pretty much my high school career, I think. So there's my bad dad joke for the day. So I'm not running on a lot of sleep, but that's what I'm going to go with. So that question 2, Tony, had a lot more parts to it we can get to, but I want to jump ahead. We're going to do one more example. We're at 9:45 right now. We're going to do one more quick example because we haven't seen anything with the table yet. So I want to make sure we address this. And this BC3 has 5 different parts, all kinds of questions that take you through the whole gamut of A, B, and BC. And so make sure you go to that link on the video that Tony showed at the very beginning to get these resources because there's so many good problems here that if you can download these and you can do these problems, man, you know that you are going to be ready for this AB exam this year, at least in terms of integration, right? It's more on the exam than just this integration stuff, but if you can do these problems, you're going to be right on top of it. So I want to make sure that we see at least one table problem so you can see the table and then you realize there's more parts to this, right? So now we have this function f is twice differentiable with a domain of x is greater than or equal to -10, and we know that f is positive for all bets of x in this domain. And it has this horizontal asymptote. Just like before, we have some information here. It doesn't really seem relevant right now, but it'll come back later in the other parts. This asymptote especially is kind of a neat little idea that will connect some stuff from AB as well. And then we have another function g that's twice differentiable. So we have these 2 functions. All we know is they're differentiable. We don't actually know what the functions are. We have a couple of values here at the table, but then we're told here in part A that the integral from 1 to 3 of f prime of g is equal to twice the integral from 1 to 3 of f times g prime. What a really good example of showing why you have to pay so close attention to these problems because these look so similar. Just that little price got moved, right? I think some of the exams, I'm sure Tony will agree that we're scoring exams. Those little details. Students forget to put prime in their notation. They kind of misread or miscopy something small that affects the whole problem. So pay really close attention to those details. But the question, what's the integral of f times g prime from 1 to 3? Well, the product, right? So that product tells us it's probably going to be u substitution. And so u, I'm going to call that f, and I'm going to call v prime g prime. And so a lot of times we learn these rules. How do you know what u and v prime or u and dv with integration by parts? Well, we have these acronyms we'll use or acronyms like the IT or different types of things like that tell you, oh, log functions or exponentials or polynomials, all these things. Well, that kind of goes out the window when you have functions like f and g prime with no actual equations, right? So you have to understand beyond just what type of functions to use. And so we know that no matter what, u we're going to differentiate it, and then v prime we're going to integrate it. So it kind of makes sense to make u become f because I can take the derivative of that, and then g prime to become v prime because I can integrate that, and those will still be functions that are in the table, right? And so going back to our quick integration by parts, one of the integral of u v prime is going to be uv minus the integral of v times u prime. So in this case, u is going to be f. That means that u prime is going to be f prime, and then v prime is g prime, which means that v is going to be g. And so using our formula here, we're going to get u times v. That's going to be f of x times g of x, and then we're going to make sure we have our bounds from 1 to 3. I'm going to put in front of here the integral from 1 to 3. I'm going to rewrite this problem kind of small. So it's the integral of f times g prime dx equals, right, this is my solution, uv minus the integral of v times u prime. So that's going to be the integral from 1 to 3 of v times u prime. That's going to be f prime of x gx dx. And we seem like we're in this loop. Like, well, how am I going to do that? I'm going to keep doing integration by parts forever. Right, it's just infinite loop. Well, that's where the other information comes in. It told me right here in the step, the integral of f prime times g, this is just twice the integral of f times g prime. And don't forget that f times g prime, this integral right here, was the original problem. So what if I rewrote this? Okay, this original information I'm trying to find, right, question? What if I just call that I, like I for integral? The integral of this problem is going to be equal to f of x times g of x from 1 to 3 minus, and then we just said that this piece right here, this integral, is equal to double this integral. Remember, this integral here was just the original problem. So really it's minus 2 times I. We're trying to find out what I is. So if I were to add 2i to the other side, kind of treat that as an expression of a variable, I get 3i equals f of x g of x from 1 to 3, which means that 3i, now I can evaluate my integral, f of 3 times g of 3 minus f of 1 g of 1. We can go to our table, I start trying to plug in some values, but f of 3 has a big question mark there. And actually, we're not going to do this problem. In part B, I think you actually have to have some more information that will help you find what f of 3 is, but we don't know what that is. So how are we going to solve this? Well, luckily for us, g of 3 is 0. And so that means that without even knowing what f of 3 is, this whole expression is going to be 0 minus f of 1 times g of 1, which is going to be, what is that, 1 times negative 4, which means that 3i just equals 4. If I divide both sides by 3, we get I is 4/3. Remember, I is what we call the initial problem. So I kind of replace that expression with the letter I, because I can combine them later on and solve it. And so this whole answer right here, I value, is just going to be 4/3. So kind of a tricky approach to a problem like that. And so you're going to see some of those neat approaches, these conceptual ideas that reinforce your understanding of these A, B, and B, C integration techniques, but in a way that's going to eliminate those devices that Tony and I keep talking about. So take a look at several of these problems on this handout, because there's a lot of really good examples that we didn't get to. That I wish we had more time. Right? I mean, we could spend 3 hours on this lesson. Neat ideas that you might see similar to what you might see on the exam. And so lots of good problems on there. Check the solutions later this evening. And as we wrap up, Tony, I know you've got a couple of tweets for us today, so I'll let you get those tweets out. But speaking of tweets, I promise you, nobody just tweeted me and gave me a hint just now. I promise I didn't get a tweet. But Perfect Strangers is my final guess.
You are the winner. Nice job. Perfect Strangers. Great physical comedy. Yeah.
Look, I knew it.
Useless trivia here. Bronson Pitcher, Mark Baker, the two actors behind the great physical comedy actors. But the guy to the left, Melanie Wilson, her father was the actor in the Don't Squeeze the Charmin commercials from the 1970s.
There you go, Tony. You're just showing your age more and more.
I know the kids, you guys don't understand what I'm talking about, but some of your teachers, you know what I'm talking about. So what do we got here for our tweets of the day? For AP Teachers Rock, and we know that all of you AP Teachers rock. We want to recognize Mrs. Sitz. She is an angel, and I wouldn't know how to do calc if it wasn't for her. She makes something so hard so easy. Thank you for all the help. Congratulations, Mrs. Sitz. You have some students that truly love you. And as far as our AP students that rock, my AP Calculus students are amazing people. I'm so proud of how hard they work and how much they care for one another. And I bet there are a lot of teachers around the country that share that same sentiment. I know Brian and I both feel that way about our own students. Good show, Brian. Good show today. Again, once you have, if you're having issues with your internet, if you're having issues acquiring hardware that you need to enjoy these lessons and ultimately take the AP Calc exam, please reach out or let a friend reach out to cb.org/text. All right, what else you got, Brian?
Not much tomorrow. I want you to make your background your favorite movie of all time this time. How about you do it post 1945? So at least we have a shot at knowing what it is. But don't show a picture of the act movie. Just maybe put a couple of clues, like a little Photoshop, some items that if we see them in your background together, we can sort of piece things together to create the movie. How's that sound? I'm going to put some more work on you.
I think I can do that. I think I can do that. All right. So on behalf of Brian, hey, thanks for joining us. We'll see you next time. And as always, we want you to make sure that you're safe, you're healthy, and keep learning.
Awesome. Pick us out, Anthony.
I am.
I was giving credit to Anthony G there.
Oh, that's right. You know what? It looks like our outro might be not working. We're going to have to fix something out, but we can do it ourselves, Brian.
Yeah.
AP Calc. We'll stop with that. Thanks for joining us, everybody. We'll see you next time.
The work with USUP. If it's not USUP, we start thinking about the little branches of different types of problems we can see. If it looks like a product, then we don't have a product rule quite per se for integration, but we do have integration by parts. This is going to be an integration by parts problem. And so integration by parts, remember the formula is going to be the integral of u times v prime is going to be equal to uv minus the integral of v times u prime. And you might have seen it a little bit different. Might have said u times dv. That's fine. You could do f times g prime. A lot of different ways that teachers and textbooks will lay this out. So don't panic if you saw it a little bit differently. I'm sure it's the exact same formula, different structure. But our main rule is to identify what u and v prime are. And so we're going to in this case set u equal to 2x and f prime equal to v prime. I chose that because in general, it's nice to make the u something that if I took its derivative, eventually that expression would go away, right? So if u is going to be 2x, if I differentiate 2x, eventually the whole thing is going to go away by turning into 0. And then v prime is going to be f prime of x dx. And then we want to find u prime, so 2x's derivative is just 2. And then we want to find v, the integral of v prime, which is just going to be f of x, right? I should probably get rid of that dx. There's no need for a descriptor there. So v is just going to be f of x. And so now that we have this, let's kind of go back to that idea furniture. I like the example Tony used with Taylor polynomials because we're going to build, right? We're going to assemble our integration by parts formula that for integrating uv prime is going to be uv. So in this case, u times v is just going to be 2x times f of x. And we're doing a definite integral from 0 to 4. So don't forget to evaluate that portion. Minus the integral from 0 to 4 of v du. So v times du is going to be 2 times f of x. I'm going to use the property to put that constant 2 in front, and we're going to integrate f of x dx. And now we're ready to just evaluate the first part, right? From 0 to 4. So for this first part right here, we're going to get 2 times 4 times f of 4 minus 2 times 0 times f of 0. And then we're going to subtract. And I'm going to have 2 times the integral from 0 to 4 f of x dx right there. So I'm going to hopefully evaluate this a little further. Remember, on the AP exam, you don't have to reduce or simplify your arithmetic, but it needs to be an answer that we can type into like a regular scientific calculator without seeing the whole problem. Well, we don't have that yet. We have a lot of variables. These functions of f aren't going to work. So I got to fill in what I can here. So we get 2 times 4 is 8, and then f of 4. Well, luckily Tony's coffee stain didn't ruin the whole problem because I can barely reach out there and see f of 4. This is a graph of f. So f of 4 was 3. So Tony, you didn't ruin the whole problem. Although I have a feeling I got Tony back a little bit because the ones that he's going to walk us through, I think his coffee stain blurred the image. He's going to figure out some stuff. I think the punishment fits the crime in that case. And then luckily for us, 2 times 0 times f of 0. This is going to be 0 because of this right here. And then minus, and now we have this 2 times the integral from 0 to 4. Oh, actually, it did come back to bite me a little bit, didn't it? Because I don't know what the integral from 0 to 4 is because it's blurred. How the heck am I going to evaluate this? I can't see what the graph is. And all of a sudden we realize there's a little bit of information here. Hey, look at that. We just actually told you the integral from 0 to 4 was 8. So we were able to finish off this problem because we're going to get 24 here minus 2 times 8. Since we know the integral from 0 to 4 is 8. And 24 minus 16 is 8. Our final answer here is just 8. So right off the bat, we kicked it off with a nice BC only type integration by parts problem. But now we're going to transition to a couple more parts of this problem that are going to be some different techniques, right? So Tony, do you want to take us through a couple of these here and kind of show us how the AB problems might show up on these?
Let's do that. So as we just indicated, when we move into part B of this problem, we're going to be shifting gears and talking about some integration techniques that you learned far before integration by parts. So our stem is the same. My mistake is still there with the coffee. And we're now asked to find the definite integral from 1 to 2 of x times f of x squared minus 1, the composite function f of x squared minus 1. And so when you investigate this a little bit, you start thinking about what integration techniques you want to use, there's certainly nothing wrong with starting early. In other words, start with the ones that you may have seen first. And if you think that you can perform a U substitution and pick the correct U and have its derivative show up elsewhere in the integrand, then that's going to alleviate all the processes of you eliminating some of those more advanced integration techniques. So in that very vein, we see that we can let U be this x squared minus 1. And of course, the reason why we want to make that choice is because the derivative of that U is going to be 2x, and we can swing over our dx if we so prefer. And completely optional. I know that this is probably getting a little bit rudimentary, but if you wanted to solve for dx just to make sure that this is the right substitution, you see that you would have this dx replaced by du over 2x, and that's what causes these x's to cancel, right? That's the whole point of this procedure. And moreover, you see that you're going to have a 1/2 that's going to jump out in front of your integrand. Sometimes with my students, I say, well, that means you're going to offset with a 1/2. So this integral expression that we have here is just going to be rewritten as 1/2 times the integration of f of u with respect to u. Okay. Now let's talk those limits of integration. Let's figure out what are we going to do about that 1 and 2. We certainly don't want to keep them into this part of the problem because those are values that pertain to the independent variable x. Do you see any more x's in our new integration? Well, of course not. So what that means is that we want to change these so that they become values of u. And so I'll work on the lower boundary first, the lower limit 1. And by simply evaluating this expression u, where x is now 1, we're going to be able to come up with a new version of our lower limit. In that case, it's going to be 0. And we'll do the same thing with our former upper limit of 2. 2 squared minus 1, of course, is 3. So now all we have to do is make sure that we put them into their correct positions. So we can figure out what the antiderivative of f from 0 to 3 is. If we can figure out a way to evaluate that new definite integral, we're in business. That's where we encounter a new problem. And the reason is because we have this terrible graph that just won't allow us to find any area underneath the curve from 0 to 3. Again, I apologize. But there are a lot of pieces of information in the stat that we can use. And you want to rest assured that if you have information in the stat that's given, you're probably going to use it at some point in that free response question. So we do know that the integration of f from 0 to 4 is 8. In other words, maybe the area under the curve all the way from 0 to 4 is 8. And then we have this little piece here, this 4 to 3. Well, one of the ways that you can think about this is there's this property called the additive integral property. And if I were to write that up here just very, very informally, I won't use proper function notation or the dx, but just to kind of lay out the idea. It basically says that if you want to integrate something from 0 to 4, let's say, okay, well, I have 0 to 3 in my answer. Well, why don't I take that into consideration, but realize the fact that I'm a little bit shy. I need to continue and add some more area, so to speak. And so I can pick up where I left off at 3 and take this all the way to 4. And now I have a true statement there. Now, if we start thinking about, well, what does this mean in terms of the picture and area per se? Well, what we know is that if we were to integrate all the way up to 4, all the way here, and I'll just write this below the graph, our stem says that that area is going to be 8. Okay. Well, I notice that I've got this other little piece of information here. Antiderivative from 4 to 3, f is negative 3. Well, if I were to partition this off even more, let's say here at 3. Now, I have to do a little bit of thinking here. We have another wrinkle in this problem, in that these boundaries are a little bit backwards than what we're normally used to seeing, but that's not a problem because we just swap them. We know that we can then just take the opposite of that result. And it sort of makes sense with this picture that we could construe that this area is 3. Okay. So if that's the case, then the area that's going to be underneath this curve that I can't see, that's going to run from 0 to positive 3, has got to be 5. 5 plus 3 is 8. So that's your visual representation of really what this additive integral property is saying. So we're able to invoke a lot of integration properties into this problem. Good morning, everyone, and welcome to AP Calculus BC Live and our wonderful presentation here about BC integration techniques. We certainly welcome those of you across the United States, our neighbors to the north from Canada, and we want to extend a particular welcome to any of you that are watching outside of North America. It's so great to have you here, whether it's live or if you're watching the recording. And as I said, we've got a very interesting presentation here today. BC integration techniques was certainly a bit of a challenge to try to integrate into this new fabric of the 2020 AP exam. But with the help of my amazing colleague Ryan Passwater, I think we were able to put together some questions that kind of capture the vibe of that particular lesson. Sometimes when I work with Ryan, I can't help but think it's almost working with a Paul McCartney or a John Lennon, the way that he can write some of these questions, and I try to stay out of the way sometimes, but then other times I try to invoke a little bit of help here when I can. But I think we've got some really interesting things for you guys to take a look at, teachers that you can share with your students, and of course students, things that you can certainly work on over the next few days to get yourself prepared for the exam. As always, you can find our materials that are associated with any of our videos in the description below the video. You still have a little bit of time if you need to call that up and maybe print that out for use in today's lesson. So, well, what do you think, Ryan? Are you ready to take care of this today?
Tony, I'm ready to go. And then at the end of yesterday's lesson, I hope that people who are watching yesterday's lesson, because it was such a, I think, a good review of that Unit 10 Convergence and Taylor Polynomial topic, and what's going to be tested on the exam in this new conceptual way. But at the end of the lesson, I challenged you to change your background to your favorite show. And I can tell by looking at this, this is definitely an older show. And then based off of your references, you gave me a Paul McCartney and John Lennon references, so I know that you like the old school stuff. So do I get more than one guess at least? So, how about this? Let me guess now, and if I'm wrong, then give me another chance. All right, so if you're watching, yesterday I asked Tony to make his background his favorite movie or TV show or something like it is. I know Tony pretty well, but it looks like I'm gonna guess Morgan Mindy.
You're pretty close on the era. You're maybe a little early, but not quite.
Okay, so that's not Robin Williams in the background, is it? I thought that was Robin Williams. Okay, well, all right, I'm gonna think about it. If you're watching, see if you can guess what it is. If you're a student and you can guess this, I think your cool points just went up about 100. And 100 is pretty good, right? In terms of the ratio, I think 100 cool points is like 7 stars in the conversion. So I'm gonna think about this more guess later. But moving on from that, what do we have coming up this week and today?
Well, let's take a look. Our schedule today, as we said before, is going to cover all things integration, both on the AB side and the BC side. The name is a little bit deceiving like that, but Brian will kind of go into detail with that. And looking ahead this week, we've got what I really enjoyed, two more enjoyable topics: the Euler's method approach to approximating the solutions of a differential equation, and logistic growth, kind of a very common theme that we've been discussing over the last several months. And then, of course, the arc link, that's more of the rectangular version of arc link, not to be confused with our parametric version that we began one of our earlier lessons with. And of course, that leads into our connecting AB to BC the following week. So I believe you are all very aware of the May 12th AP exam. So we'll share a lot more detail with that exam as time draws near. But as of right now, we want you to realize we're talking about 2 free response questions on this year's exam. And so that's what you're going to see from Ryan and I over the next several days. Lots of free response questions. In some cases, we'll do all parts of one. In some cases, like today, we might do bits and pieces of one to kind of get our topics across. But that's what we're looking at, free response questions. Ryan, what do you have in terms of the overall makeup of today's lesson?
Sure. So we're talking about BC integration, and I think there's been a little bit of confusion. I've seen this on some different groups I'm in with teachers, especially, where we know this year because of the exams, the shortness of the exam, only 2 FRQs. The BC exam is not going to be an AB subscore, right? You're going to get 1 score for BC. And I think some people have interpreted that to think the exam's only going to have those unique BC only questions on it. But that's not going to be true. So additionally, whether you know this or not, a normal BC exam, 60% of the points, so almost 2/3 of the questions and points, are AB topics, and then the other 40% are those additional unique BC topics, right? We're not going to have an AB subscore, but we're still going to see a pretty close ratio like that. So it may not be exactly 60-40 this year since they took out some of those BC topics from the exam. But maybe let's just say it's 2/3 of AB and 1/3 of BC or some kind of ratio like that. But the majority of points, the majority of questions are still going to come from those AB topics. And so today, as we talk about integration, we're going to look at those BC only kind of unique topics. We're also going to see AB topics mixed in because all of this is going to be together on the exam. I'm not going to delineate them for us. They're going to be mixed in, and we're going to have to choose our procedures. And so these are all the integration things we might see on a typical exam or Calc BC. They all come from Unit 6 if you have the CED or course exam description. We're looking at applying some properties of integrals. I think that one's going to be really key this year because with the exam and trying to write questions, so there's no calculator advantage or no Google or text advantage or Photomath type advantages. Properties are a really good way to get around those sort of advantages. So look at those. U substitution and then integrating with long division and completing the square. We won't actually see any of those problems in this lesson. So use a very small small topic on a typical year. Integration by parts, partial fractions, and improper intervals. Those three are going to be the BC only ones. So 20 put little stars by there. And if you've done partial fractions, we wrote in there in parentheses non-repeating linear fraction because it's only a small type of partial fraction problem that we see on the Calc BC exam. Even though a typical Calc 2 course might cover multiple different varieties, we're going to do what we call non-repeating linear partial fractions. It sounds like a pretty fancy phrase, but it's actually a lot easier than it sounds. So looking at that, this is our 2020 FRQ practice with integration. So here's the first problem. And we wrote this. Tony, I wrote this problem. I thought it was, what is that? Okay, so it looks like it's a smudge. I'm not sure what on there. So we have here a graph from 0 to 5. It says the function f is continuous and differentiable. A portion of the graph of f of x is supposed to be a graph of f of x. When I made it, it was nice and pretty. Oh, that's right. I remember this now. It was obscured by a Tony record coffee stain. Tony,
Sorry.
I told you to not drink coffee when we were this problem. But so anyway, Tony kind of goofed this problem up, right? We had a nice pretty graph. I spent a lot of time making this, and then he spilled a bunch of stuff on the graph, and now I didn't save it. And so we have this obscurity. So I'm not sure what's going on in the middle there, but we do know we did figure out. Remember doing this. The integral from 0 to 4 of f is 8, and the integral from 4 to 3 of f was -3. And we also know that f is linear, right? It's a straight line, linear function between 0 and 1 right here. And it's also linear between 4 and 5. Now we don't know what's happening between there. In fact, it's not going to be linear, unfortunately. If it was linear, it wouldn't be differentiable everywhere, right? Hence a good mean value theorem connection, right? That we could not guarantee a slope, right? Let's talk about that. So check out that when we do the connections from A to B. This problem might make a reappearance. And when x is greater than or equal to 5, f of x equals this expression. So we don't see the rest of this graph, but it does continue somewhere. And it continues with this function. We don't know what A is. So there's a whole lot of information in the stem, right? I put a lot of information there because we have 4 parts to the problem. So we're not going to use all of it up front. And one of the things I mentioned yesterday in our lesson, our review topic for the exam on Unit 10, Convergence and Series, is sometimes we focus so much on the intro information, we get overwhelmed. Instead of just going to the question, trying to deconstruct or break it down what the question wants. And so part A says, what's the integral of 2x times f prime of x? I would tell my BC students, when you see integration problem, your first mental idea should be, is this going to be a U substitution problem, right? Can I do U sub on it? This is not.
Calculus. Taking polynomials. Infinite series. Differential equation. Calculus. Taking polynomials. Infinite series. Differential equation.
Welcome everybody. We are continuing our AP Calculus BC exam prep for the 2020 year. So glad that you're joining us today. Today we're going to be talking about approximating solutions using Euler's method. Throughout today's lesson, we're going to be not just looking at some Euler's method type FRQs, we'll be also looking at how this might connect with other AB and BC topics on this year's 2020 exam. So if you haven't done already, don't forget at the bottom of each video, you'll see a little link there where you can access our resources. You'll see the folders that Isaac Newton has shared that with you. You can download those, print them off, follow along with us. And as always, there's a whole bunch of additional problems in those materials that we want to get to during our live lessons. And all those problems are unique, new, and designed specifically for that conceptual understanding to get you ready for the 2020 AP Calculus BC exam. So my name is Brian Passmore. I am here joined by my awesome co-host Tony Becker. Tony, how's it going this morning?
I am doing fantastic. The sun is shining here in the Midwest. We have a great lesson here over Euler's method, and we're joined by a few thousand of our closest friends who are studying BC calculus both on the teacher side and the student side. So I couldn't be better. And I did my homework. Brian assigned me a homework assignment where I was supposed to use a image of my favorite movie of all time and use it as my backdrop. So here it is. What do you think?
Yeah, so I've been giving you some homework assignments, and I think I got this one already. So last time it took me the whole session, but I'm pretty sure I got it figured out. I'm going to go with because you're a musical guy, right? You play the guitar, you've been in lots of bands. I've heard you sing, I've heard you perform, and so based on that, I'm going to guess. And you're pretty old. I'm going to guess. I'm going to guess. Sound of Music is my guess.
Okay, well, you're close.
No?
It's an outside rolling meadow. Yeah, that's my wife's favorite movie. However, this is not a scene from the Sound of Music. If you look closer at the animals, that might give it away. I'm not so sure there are too many of these animals in Austria, perhaps. But I'll give you a guess or two later on.
Okay, do me a favor, maybe if do you have any other like backgrounds? Because I'm already thinking I'm never going to guess this. Do you have anything else queued up that later on? You give me like a second hint or something like that?
I'll tell you what, I think I can find one while you're doing the problem later on. So I'll make that deal with you.
Okay, so I'll think about some more. Until then, do you want to get us going on what we're looking at today, this week, and then coming up?
Sure can. What we have got going on today, obviously, is Euler's method. And looking ahead to the next couple of days in the week, we're going to follow that up with logistic growth tomorrow and arc length Friday. And it's really important that you understand that we're going to really work hard to take previous ideas that we've talked about already and embed them into these newer ideas. So even throughout today's lesson and on into this next week and even beyond, you're going to see, say, convergence and Taylor polynomials, maybe some integration techniques possibly infused into some of these newer ideas. So you don't want to just look at the upcoming calendar and say, I know everything there is to know about logistic growth, because you can see how we merge some of these ideas together and we create this more evolved free response question. So keep that in mind as you are moving through. As we look into the future, we know that May 12th is our AP exam. We know that it's going to consist of 2 free response questions. So you always want to keep that in your mind, and we'll go into a great deal more detail with that test structure as the test draws near. As far as today's lesson, it is centered around a wonderful mathematician named Leonhard Euler. It is pronounced Euler, not Euler, as in Euler. He is a Swiss mathematician, and he just had so many contributions to the mathematics world. His mathematics that he did applied to physics. He wrote treatises on shipbuilding and optics and acoustics and astronomy and mechanics. So he's certainly renowned as one of the greatest mathematicians of all time. In fact, I think it was last week that Brian had a list. He composes a top 50 list of his all-time favorite mathematicians. Sometimes they fluctuate. So Brian, where does Euler fall on your list?
Yeah, he's one of my all-time favorites. I love the last line on the screen that says he's regarded by many to be the greatest mathematician of all time. He actually comes in number 4 in my top 50 list. And I put that in the Dropbox. I think last week we talked about my top 50 list. So he definitely is in my top 5. So many amazing things about him. It's kind of interesting because he gets this Euler's method, credit for this. This is not even near the peak of all the things that he's contributed. I think I remember that he is the most prolific mathematician of all times in terms of producing volumes of work and papers. So, but even with all that genius, all that incredible talent, I think my favorite thing about Euler, my favorite anecdote was I remember reading one time. I hope I have the right guy because we didn't plan this out. So it's always tricky when you're going live on the air because you might say something that's wrong and we get all those emails correcting us. But I remember reading, Tony, and tell me if I'm wrong, that there was a time when he got really old and he lost vision. Like, he ended up going the line, but he was still doing a lot of mathematical work because he had such a photograph memory. He would just dictate to his assistants or students or whoever was helping him. And he had everything kind of memorized and know where he's going. And they were just writing on paper everything that he was doing. So he was still producing mathematical genius as a blind mathematician later in life. That's not right.
Very true. I've read that same thing about him. You may not know this, but I bet your teachers do. But many of your students do know. The number E is called E for a very important reason. It's this guy right here. So
I like all the E because he used the letter E for the symbol. So Yes. Anyway, so Euler's method we're going to talk about today. And so Euler's method, and we're not going to, during these review sessions for the exam, we know that you've already covered these materials, right? So the previous 2.5 weeks, we were teaching lessons from Unit 9 and Unit 10, Parametrics, Convergence, and Polynomials, because we knew that a lot of schools, and most schools probably, didn't get a chance to cover those topics before students were sent home for distance or e-learning. And so Calc, we're going to make sure that you had some lessons to introduce those topics to you. And this review stuff that we started this week and that will continue all the way through during the rest of these sessions are a little bit different in nature. That's why Tony and I are co-hosting these, but these are covering topics that we're assuming you have covered before, right? So we're not going to be teaching a brand new lesson. You're not going to see us teach Euler's method today from scratch. We're not going to teach logistics or arc length or things like that, because we know that you probably have them. We're going to kind of just jump right into AP exam review. And if you're thinking, oh my gosh, we learned Euler's method a long time ago, I've forgotten that. Well, we're going to, in our examples, refresh and remind you how to do it. But there's a reason why we're not going in depth with our lessons. So Euler's method is a numerical approach to approximate a particular solution, right? We've done differential equations, and in AB, we learned how to separate and integrate, right, to solve particular solutions or even general solutions for differential equations. But there's a lot of differential equations that you can't solve for, or you don't have enough information to solve them. And so in that case, how do you find solutions or approximate stuff? Well, we do that one way is using Euler's method. And what it does is it takes a nice little twist. I always think it's like an intermediate between tangent lines and Taylor polynomials, right? Where you take a tangent line approximation. A tangent line approximation would be as opposed to Euler's method of 0 steps, right? But it's Euler's method idea where you can take a tangent line to a graph, and then we realize that this graph keeps curving, right? The graph is changing. Once we pick our tangent line, we're sort of locked in on a way to adjust. So the further out we go from that point of tangency, the less accurate we get. But then instead of being stuck on this path forever, we're able to sort of stop at our own discretion and then readjust our tangent line to say, well, this tangent line is not going so well, but I can adjust my slope. So this graph had a different slope, right? The graph is turning, and the graph now has a tangent line here. But I don't know what that point is on the graph, but I can maybe figure out the slope since I have the derivative. And so I can, from that point on, recreate a new tangent line. And we can keep adjusting these tangent lines because we have the derivative. And we can take our tangent line, come up with this little value, this point on our tangent line, and we can use our derivative equation to readjust the slope, create a new tangent line. We keep doing that indefinitely. It kind of mirrors the shape of the graph, right? How often you switch your tangent lines is called the step size of Euler's method problems. So Tony and I today are going to be looking at a couple of problems in context of the AP exam, and we do it very differently. As we were planning these sessions, we had some discussions of should we try to be uniform in how we tackle, how we approach these problems, but we decided no. So we're both going to do these problems how we show our own students. And so we're doing that because we know there's a lot of different ways teachers approach this topic. And so if I'm doing it one way, it might look familiar to you. It might be like, that's not how I learned it, right? So when Tony does his method, that might make more sense to you, or vice versa, right? And so we're going to do them both ways. You can see the different approaches, and both valid, both perfectly correct. If you liked, or if you've done my approach before, then when Tony's doing his example, see if you can see what he's doing, because I think it'll make it a little bit more understandable and help the ideas more. You can go back and forth between our two methods, right? So don't be too caught off guard if we're doing these a little bit differently and how we set them up. But we're doing the same thing in the background. We're both using those tangent lines. So this is a traditional FRQ covering Euler's method. This is what you might have seen in years past, right? You might say something like, consider the differential equation dy over dx equals 4x squared plus y, and y equals f of x is the particular solution with the initial condition f of 0 equals 2. You use Euler's method to kind of give you that suggestion, starting at x equals 0 with two steps of equal size to approximate f of 1. So this is a good example because in our A, B, and B, C classes, we don't have a way to solve that differential equation. We can't separate, we can't solve it to find a general solution. There are techniques to do that. You might have heard about integrating factors or other ideas, but we can't solve it with what we know in Calc A, B, or B, C. And so we can't find f of 1. We don't even know what the graph of f looks like. But let's just say for our purposes, the graph of f looks something like this, right? This is pretend looks something like that. And all we know is the derivative and the starting point, right? We have f of 0. So what we're going to do is we want to approximate f of 2. We want to know what is f of 2 on this graph. And so we can take our tangent line idea and say, well, we could make a tangent line here, right? Because we have a point and we have a derivative, so we can find the slope. But then instead of just using the tangent line, knowing the graph of f could make a lot of twists and turns, and our tangent line may not be very accurate, what if we adjusted, right? We have two steps. What if we adjusted halfway through and then redirected our graph to take on the shape or the direction of our original function, right? And so we can do that because on the original graph, we're going to be able to figure out not what that point is on the graph, but at least what the derivative is when x is 1. And so we can use this, and then we can figure out what this point is right here. So this is what we're going to be approximating. We're going to approximate f of 1 by coming up with, I already realized I drew this wrong, didn't I? It should have been 0.5 and 1. We're doing two steps. I was thinking f of 2. I think I saw 2 here. I got a little mixed up there. So Tony, feel free if I do something wrong, you can go ahead and stop me and correct me, because otherwise it's leading in infamy. I don't know the problem wrong like I did a couple weeks ago on live YouTube. And so here's how I like to set this up. Now that we have this visual idea, I'm not going to draw that graph every time, but I want to remind you kind of what's happening behind the scenes, because we're going to get into a lot of formulas and things like that. Sometimes we lose track of what we're really doing. So I like to use what I call the box method, and you might have your teachers do this. And Tony will show you another method that looks a little bit different, but really is doing the exact same thing. So I create this box. I call this top row in, and then the second row is going to be my x's, so x of it and then y's of it. And depending on how many steps we have, that will determine those n values. So we always start at n equals 0. You're starting n value. And then we're doing two steps. So we're going to go 1 to 2. So this is kind of which step you are on is our n value. And then our x of n would be the xy coordinate, right? So we're starting right here. So we know that x was 0 according to our coordinate, and y was 2. And then now we want to come up with what that next point is on the line. We're going to figure out what that first kind of halfway point is. And so the step size is, if we're doing two of them, and we're trying to approximate f of 1, we know that our last x coordinate has to be 1. That's what we're trying to get to. If we're doing two steps, starting at 0 and going to 1, then the middle step, x has to be 0.5, right? It's going to be equal size steps, so it's going to be 0.5 and then 0.5. So we can always figure out our x values pretty much right away. The trick is finding out what those y values are, right? And so we have this little formula. If I want to know the next y value in the box, we'll call that y sub plus 1. That's always going to equal your current y value plus your step size, which we're going to call this h, will be our step size, times the derivative at your current location. You might recognize this. It looks kind of fancy and complicated, but really this is just a tangent line equation, right? We have our y is going to be our initial y value plus the distance we travel times the slope. So really this is another way of doing tangent lines. So Tony does his approach. You're going to see pretty quickly that he's doing that exact approach, but in a more direct way with tangent lines. So if I want to find y sub 1 in this case, it's going to be my initial y value, which was 2, plus our step size, which was 0.5. That's what h is. We said, right? H is 0.5 because we're doing 0.5 each time. And then we have to find the derivative. This is the big key, is we use this differential equation for our slope. And so we're going to find the derivative at your current location. So we're using this green tangent line. So x is 0 and y is 2. So our derivative when x is 0 and y is 2 is going to be 0 plus 2, which is just 2. And we get 2 plus 1 for a total of 3. So our y value here is going to be 3. And then we're going to do it one more time. So if I want to find y sub 2, my last y value, now we have a new y value. Now we're sitting right here, right? At this point, so my current y value is now 3. And then our step size never changes. It's always going to be 0.5. But our derivative now is different, right? We have our equation 4x squared plus y. But remember, we have this coordinate here. Our new coordinate is 1/2 comma 3. And so we have to plug our current point 1/2 comma 3 into our derivative and then evaluate that. And so this was a multiple choice question, which a lot of times they have been in the years past. We don't know exactly what this year's exam is going to look like, but I would be pretty confident saying this will not be on this year's multiple choice test. I'm sure Tony would agree, since we have no multiple choice test this year. 4 times 1/2 squared is going to be 1 plus 3, and then 3 plus 1/2 times 4 just gives us 5. So our value here is going to be 5. And so that's what we just calculated right here, which tells us that f of 1, according to Euler's method, is going to be approximately equal to 5, right? So this is kind of one method to do. It's going to be really important, especially with free response questions, that if you use a table or use this method or use a method that Tony is going to show you here in a second, make sure your work is labeled, organized, and clear what you're doing, right? You're telling a story with your work, right? You're trying to tell the person grading your paper what you were thinking, what you were doing, so that way we can award you all points that you deserve. So I mentioned, Tony, that this is probably not going to be on this year's multiple choice, seeing how there's not a multiple choice. But this was a traditional FRQ. I'm thinking this might look possibly a little bit different this year. It might look like this, or it may look slightly different. Would you agree with that?
I would certainly agree. 3. And as we move to our 2020 FRQ practice, when you see BC1, I think it'll be very evident just within the first line of what that difference is going to entail. So if you look at this and read it together with me, it says let k be a constant. Well, there you go. Consider the differential equation dy dx equal kx squared plus y, where y equal f of x is the particular solution to the differential equation with initial condition f of 0 is 2. So it reads very similar to the problem that Brian just did, but instead of that 4 coefficient from the x squared, we have this arbitrary k. So now any kind of computer algebra system manipulator won't really get the job done in terms of trying to program in some kind of a sophisticated algorithm to figure out this particular solution. So our directive in this problem, using Euler's method, start with x equals 0, 2 steps of equal size. What we're going to do is, and I'll make sure I share my screen so you can see this. You're probably following along with your paper, but hopefully now you can see the screen where this dy dx is now k x squared plus y, right? Here's our differential equation. You can see the difference here is the fact that we have that k, all right? So what we want to do is use Euler's method, starting with x equals 0, 2 steps of equal size, and knowing that f of 1 is approximately equal to 17/4, we got to kind of backtrack and figure out what that k is. So like Brian said, we're going to show you a couple of different methods to set this up. Both of these methods I use in my class, the one, a very similar one to what Brian uses, and then I also tend to use this one for some kids that might have a hard time with the structure of what Euler's method is all about. And this is going to favor the kids who maybe are really good at writing equations of tangent lines but have a hard time piecing together what Euler's method means. So we're going to start off with our point. We are given a point 0, 2, right? That's our f of 0 equal 2 that was given. And we are going to figure out what the slope is. Well, we would hope that any good BC Calc student, any good AB Calc student would know that the slope is the derivative. So if we go to this derivative equation dy dx and we use the fact that the x is 0 and the y is 2, we'll very quickly come to the conclusion that k times 0 squared plus 2 is going to give us that slope of 2, okay? Well, what can you do with a point and a slope? You can certainly write the equation of a line, and it is a tangent line at that point. And this one's a pretty easy one to do because don't we really just have a y-intercept there? So what we could do is just use y equal mx plus b, right? A little bit faster maybe than using point slope form, and only because we have this 0 there. All right, now this is where things start to get a little interesting because we have to acknowledge this idea of the step size. So if we read back, we see that there are going to be 2 steps of equal size. We start at 0, we want to end at 1. You basically find the difference between 1 and 0 and divide by how many steps, and that will tell you that your step size is going to be 1/2. Okay? So that's going to indicate that our next point, our next row, our next iteration will have that step added to the x. So you always want to add the h to the x value in this particular point. Now we have to address, well, what is that y point? Well, we take that new x and we apply it to our previous tangent lines equation. So sometimes I might write another column over here and I'll call it the new y value. And the new y value here is just a matter of, like I said, replacing the x with my newer x 1/2, and we end up with 3, and that's going to get carried over here. And that's really it, right? That's the process. You just repeat it as many times as you need. So we go back into the slope. Now something's very interesting is going to happen to the slope now. If we let the x be 1/2 and square it, we have a 1/4 that's going to be multiplied by the k. We don't lose that k value now. And of course we add the 3, right? We still plug the 3 in for the y. Now that might seem like a very unusual slope. Well, let's be honest, it is a very unusual slope, but we stay the course. We have to use the point slope formula now. So y minus the y1 equals the k value multiplied by the quantity x minus the x1. And so now we have a brand new equation of the tangent line, albeit a little weird in terms of this k. I just really briefly want to talk about notation here. I had a professor one time in college that was not very happy about students organizing their work with Euler's method like this because we're using a new instance of y and x that depicts a completely different tangent line. And so we were directed to maybe use subscripts. Use subscripts of 1 for the first iteration, use subscripts of 2 for the second iteration. I don't necessarily require that my students do that. It is a more powerful, stronger way to communicate what you're doing. I don't see that on the AP exam that you would have to do that. If you think about this as being a restart for each of these steps, you're certainly going to be fine. But if you want your notation to be a little bit more prim and proper, the use of subscripts is not a bad idea. Once again, we're going to apply that step size of h, which is 1/2, which takes us to our x value of 1, which is a good thing, right? Because this is the value that I guess we're used to like solving for, right? But the problem is we know that value, right? We know that that value is going to be 17/4. That's the approximation that was given to us here in the question. But we want to figure out what is the k that's going to make that happen. So if we revisit our previous equation of our tangent line here, right here, we can then solve that for k by using the 17/4 as that new y, where 1 is our x. So what would that look like? Well, you could say something along the lines of f of 1 we know is an approximation of 17/4, which means that that is really the same thing as y2 evaluated at that 1. Well, if I go ahead and rethink what this y2 expression looks like, I have 1/4 k plus 3. Now this x2 is going to get replaced by that 1. 1 minus 1/2 is 1/2, and I don't want to forget that there was this minus 3 in the front that I'm going to add over here to that side. Okay, so what do I have here? If I just scroll down a little bit, I'm going to bring down that 17/4, and then I'm going to work this expression out. Well, actually what I'm going to do is I'm going to subtract 3 over from this. Just want to be careful because really at this point it's just some simple algebra, but simple algebra is also just as easy to mess up as complex calculus. So 17/4 minus 3 is going to be, I believe that would be 5/4. That 5/4 that we have there, let's multiply the 2 over. That way we get 10/4 or 5/2. And now we can solve this for k, hopefully pretty easily, right? We'll call this 5/2. He's going to have a dream. I'm dreaming about being called 5/2. How's that? And if I subtract 3, which is 6/2, right? So 5/2 minus 6/2, 6/2 is -1/2. And then my final step would be to multiply both sides by 4. And we see that k is -2. So it's a very similar process that what Brian showed. It's just structured a little bit differently. And of course, it's now under the guise of a slightly different style of FRQ that is going to involve finding this value of k. So I think Brian's going to go ahead and take you through BC2, if I'm not mistaken. Is that right?
Yeah, absolutely, Tony. Thank you. So I'm glad that you guys got to see 2 approaches because they really are the same thing. And if you understand Euler's method, then you can make those connections. Because in a lot of the previous years, you might see some multiple choice questions where we're not going to see your work or how you're organizing things, and you can get those answers pretty easily. Sometimes you guys can do it in your head, kind of some scratch work. But now, since they're all FRQs, you certainly have to show your work in a very organized manner. But also, we're going to have some more conceptual problems where having your work organized is not just going to help you be eligible to earn the points. It's going to help you solve problems that look a lot different than a typical problem. So BC2 is an extension of what Tony did, where there's kind of k values in, but kind of in a unique way. So being organized is going to play a big role in making sure we can get this problem correct. So I went ahead and kind of created my table on here from before, and then I wrote a little kind of model equation that we're going to use. And so we have this table of values, a lot different approach. So we don't have a lot of information, but we're given different information than we normally have, right? Normally we have our x values and our step sizes, and we're told what to approximate. Whereas this problem, notice the table, they actually gave us all the y values, right? They told us what the answers were. So we're not really approximating anything. We're trying to solve some other stuff in the problem. So we have this new differential equation, k times x minus y minus 2x squared, where k is a constant. And then we also know there's this condition f of 0 equal 1. So we're going to use Euler's method with 2 equal step sizes h to approximate f of b. So now the problem is we don't even know what it is we're trying to approximate. Because we don't know what we're trying to approximate. We don't know how big our step sizes are. We have no way of knowing what h is. And so we're going to figure out if we can solve for h and k without even knowing what b is. So now we've seen a couple examples of Euler's method. We cruise hopefully this problem after the Euler's part to get to solving for it, right? So if we were trying to use Euler's method, what we did, we first try to figure out our y sub 1, right? We have our y sub 0 given to us. Our y sub 1 would be our initial y value plus h times the derivative, right? That's how we would set this problem up. Well, in this case, what do we know from this problem? Well, we actually know what y sub 1 is. In this table, we're given those values. So let's just go with it, see what happens. So we know that y sub 1 is 1/2. That's going to be our current or our original y value plus h, which we don't know, times the derivative at the point 0, 1. So if I plug in 0 for x and y for 1 into our formula, what's going to happen if you plug in 0 for x? Those are going to go away, aren't they? All we're going to have left is this negative y term, which we actually know, right? Don't we? Because we were told y in this guy, so we just put in y there. We know that y is 1, don't we? So it's just going to be -1. So that means that we have 1/2 equals 1 minus h. And then if we solve for h here, we're going to get h is 1/2. And so what does that do for us? Well, first of all, it solve for h is 1/2, which means my step sizes are 1/2. So that means my next x value then has to be 1/2, which means the last value up here is going to have to be 1, because we're going 1/2 each time, right? And so really the problem was having us approximate f of 1. Now there's still one last piece that we haven't solved for yet. Is we have to solve for k, right? What was this k value here? How would we figure that out? Well, now that we know what our last point is, we could use that to find our k value, because we also know that y sub 2 is going to be y sub 1 plus h, which we now know is 1/2 times the derivative at x sub 1, y sub 1. And then we have all this information we can now plug in. We know what y sub 2 is. We know our y value is going to be 3. Our current y value, y sub 1, is just 1/2, and then times 1/2 times the derivative. Well, let's go ahead and plug in what we know, right? We're sitting here at this point right here, when x is 1/2, y is also 1/2. If we plug that in there, we're going to get 1/2 times k minus y, which is also 1/2, and then minus 2 times x squared, right? So if you look at that equation, there's only one variable k. We have everything else given to us, so we can use this to sort of work backwards to find that missing k value. And so if I'm solving this, I'm probably going to do this first. I'm going to work inside of these brackets a little bit. We have 1/2 k here, 2 times 1/2 squared. Well, 1/2 squared is just 1/4 times 2 is 1/2. So really we have a negative 1/2 minus another 1/2, or just a minus 1. I don't love working with fractions. So whenever I see that, one of my first go-to moves is just to multiply through, just to clear out those fractions, right? So multiply both sides of the equation by 2, and we get 6 equals 1 plus this 1/2 just cancels in, right? It becomes 1/2 k minus 1. Hey, those 1s cancel as well, and we just get 6 equals 1/2 k, which means that our k value is going to be 12. So kind of a neat twist on Euler's method, because you're not going to Google or search that kind of problem on an app on your phone or something, or find the answer in a textbook, but really still using Euler's method, making sure that you can do it in a reverse kind of manner, right? So I love that problem. And so Tony's going to walk us through multiple parts of the problem. So now that we've seen a few kind of free examples of Euler's method, Tony's going to look at a really cool FRQ that goes through a lot of different parts that connects Euler's method to a couple other things that we've been talking about.
Yes, and I think what I'm going to do with my party, I'm going to accelerate through it a little bit, maybe show you the first couple of iterations, because I think you've got the general idea about how this is an iterative process, and you have to kind of repeat the same things over and over again to get to your result. So I'd like to get to the parts that have the sort of the infused or embedded ideas from some previous topics. So if we take a look at the stem here, the function f is differentiable for all values of x. We know that f of 0 is 6, and we're given this random f double prime of 0 equals 1/4. I bet we use that at some point. A portion of the graph of f prime, the derivative of f, is shown here to the right, and the regions bounding, the bounded regions R and S have areas of 1/2, 5/8 respectively. Part A just is a straightforward Euler's method. Start at x equals 0, use 4 steps of equal size, and approximate f of 2. Well, if we set it up structurally like I did before, we would start with this initial point 0.6, and then finding the slope is really the nuance with part A as opposed to what we've seen in the previous couple of questions. Since we're given a graph of that line, the students would have to connect that means slope. So when x is 0 on this graph, we can see that f prime is certainly equal to 1. So that is our particular slope. We know that f prime of 0 is 1. So again, from that, it's fairly easy to write an equation of a line in slope-intercept form, right? Because we have a y-intercept there. And then if we apply our step size, now we have to think about that. Let's see, we go from 0 to 2, and we're going to do so with 4 equal steps. So the difference between 2 and 0 is 2, divide by 4. That indicates that our step size is going to be 1/2. So we apply that 1/2, we have a new x value of 1/2, and then to find that new y value, we have to go back to our previous line, plug in our new x, which is equal to 1/2, and then think, well, what's 1/2 plus 6? That's 6.5, or we could call it 13/2 if you want to work with decimals. You could use 6.5. Sometimes in these problems, believe it or not, I think it's easier to work with fractions than it is with decimals when you don't have a calculator. Now, as far as this slope, now we see our new x position is at 1/2, so we have to figure out what's f prime of 1/2, and that definitely takes us up here to the curve. We've got a very well-behaved curve that shows nice integer values along the y-axis for these various places that we're going to be stopping, and so we have a 2 there. So I'll just write one more line equation just to kind of give you the general feel. Here's our point slope form. But as I said, you just basically keep this process going, and when you get down to the end, just 4 iterations, you're going to end up with eventually a 2, right? By the time you continue adding a half. And I'm going to go ahead and tell you that the answer to this is 9. In other words, the approximation, that's really important. We don't ever want to say that f of 2 equals 9. We like to say that f of 2 is approximately 9 for good math notation. But let's see if you guys, for homework, can fill in the gaps to get to that answer. Now, parts B and C, I'll work with you before I turn it over to Brian, are going to be a little bit quicker, a little bit easier. And part B particularly is going to invoke some AB content. Just simply asks, use a tangent line approximation at x, 2f of x, sorry, at x equals 0 to approximate f of 2. So you kind of look at this and think, well, what does this have to do with Euler's method? Well, it's really the first iteration. I mean, that's really all it's saying. You have this point 0.6, right? It says that f of 0 equals 6. We're going to use the tangent line when x is 0, and so then we want to find the slope specifically there. So you have to know that you're looking for the slope right there at the beginning. And we've already talked about that, right? That's that value of 1. And in fact, if you put these two ideas together, you might think, well, isn't that the very first line that we wrote in part A? It certainly is. The only difference to this problem is this is where we're stopping. If we want to approximate f of 2, we know that that's really approximately y of 2, which in this case is 8. And it's interesting to see that our final answer that we got for part A was 9 to approximate f of 2, but here we got 8. And it makes you think, which one do you think might be a little bit better? The one that allowed us to redirect that tangent line, I think, 3 additional times, or the one that uses the original tangent line? So if you're thinking that possibly that part A answer is a little bit more accurate, you're exactly right. So if we move into part C, boy, found a great way to infuse some previous ideas here. Find p sub 2 of x, the second degree Maclaurin polynomial for f of x, and evaluate p sub 2 of 2. So we are writing just a real quick polynomial. It's a Maclaurin, so that means that we are centered at 0, c is 0, or x is 0, and it is a second degree. All right. So if you kind of recall our setup there, we like to say that, okay, if we're going to put this p sub 2 together, it's going to involve finding f evaluated at where we're centered, and then to that we will add f prime where we're centered times our x minus 0 to the first, or just x, and then we have our final term, which is going to consist of our f double prime of 0. That of course would be divided by 2 factorial and then multiplied by x squared. Now we just assemble and we find our f of 0, which is given in the stem here of the problem of 6, and then f prime of 0. I think this is now the third time that we're going to defer to that f prime of 0 being equal to 1 times x, or just x, and then f double prime. Well, you don't want to really spend a lot of time looking at the graph here to figure out what f double prime of 0 is, because it's going to be very difficult. But if you continue to look at the stem of the question, f double prime of 0, it indicates that it is equal to 1/4, and if you divide that by 2 factorial and then multiply by your x squared, you're good to go. And of course, if you wanted to, you could simplify this. It simplifies pretty nicely to be, I believe that would be a 1/8 x squared if I did not do that incorrectly. I think that's what we get for that part C. Right. So moving ahead to part D, I think Brian's going to take over and show you some other nuances with this particular BC question.
Sure, sounds great, Tony. So this question, so I'm not going to finish part D and E on here, but I want to make sure you know that it's there. This is why those links underneath the videos are so helpful, because there's so many good problems that you could do there. So part D introduces this idea of a geometric series. We have some convergence ideas in there, and we're going to get to do some integration techniques as well. So it's kind of a neat little problem. So take a look at it. Our friend Ted is typing up the solutions. He might have called me and Tony evil yesterday. He typed up the solutions. We'll send us some questions. Like, hey, what's going on here? And sometimes we just have errors on our initial papers. You might have even downloaded one of our documents that had a typo in it first, because we're doing these every day. We can't catch every mistake. But a lot of times it's like, man, they're tricky, tough problems, right? So and then part E goes into another idea of average value. So now we're connecting it back to some AP topics, and so our integration ideas to find the exact value of f of 6. Right? We were approximating it earlier. Now we come up with the exact value if we can use an average value problem. So make sure you try those, check the solutions, and see how they look. So what I want to do is get to BC number 4. So if you have your handouts with you, solution number 4, I think it's a really important problem. And we're not going to spend a ton of time on it because you got an idea of Euler's method, but there's a couple of twists here that I want to make sure you're aware of. Well, we see a graph in the stem, and Tony gave us a nice problem. We had a graph that we worked with the last one, but it's a little bit different. And then our differential equation, right, is x times h of x. This is what we're reading carefully becomes an important idea because our differential equation dy dx is for f of x. So f of x is connected to dy dx. If I could solve this differential equation, it would be giving me a solution for f. It just so happens that the differential equation is connected with this other graph of h. H is part of our derivative. We have an initial condition of f of 3 equals -7, right? So why is this problem so different? Well, it's not because there's a graph and a couple kind of more conceptual ideas. It's because look what's happening. We're given f of 3, but we're trying to approximate f of 0. This is the first example we've seen where we know a value of our graph at 3, and we're trying to go backwards this time instead of going forward, right? Well, what does that do? Well, it changes your step sizes, right? Not just how long they are, but the direction of them. And so if we're starting at 0, we're starting at 3, sorry, our x value is 3, our y value is -7 to begin with, we want to approximate f of 0, right? So we're going to have 3 equal steps. So we're going to go down to 2, then to 1, to 0. What does that tell you about h? Well, be careful. H is not 1, it's -1, right? Because we're going reversed with our x value. So you have to be really careful. If you're going backwards, you catch that nuance that h is a negative value in this case. So if we're trying to solve this problem, we could go, we got to find y sub 1, our first y coordinate is going to be our starting y value of -7 minus 1 in this case, right? Times the derivative at our conditioner. And that's going to be x times h of x. So we know x is 3. And then h of 3 is going to be, we're going to compute, right? And that's going to be -7 minus 1. And then we have this nice graph here to find h of 3. H of 3 is right here, which happens to be -1. And so our next y value is going to be -7 plus 3, which is -4. So we get -4 here. Then we would just continue that process, right? We say, okay, our next y value is going to be our current y value. Our h doesn't change, it's always the same. That's why they're always equal step sizes. But now we're taking the derivative at this location. So x is now 2. And then h of 2, according to the graph, is right here. H of 2 happens to also be 2. And we get -4 minus 4, which is -8. And then our final iteration, we're now at -8. And we still have the -1. Our current x value now becomes 1. And then h of 1 happens to also be 1 in this picture. And then we get -8 minus 1, which is -9. So after all of that, we came up with -9 for our approximation, which means that according to Euler's method with this process, f of 0, like Tony mentioned, is approximately equal to -9. So it's important to realize whether you're going forward or backwards, pay attention to those details. Those little details come up a lot. Like if you're doing related rates, remember like related rates and Calc way back when they would give you some rates of change, and they might slide in like something that's decreasing at a certain rate, and you had to make the connection that, oh yeah, I got to make that number negative. It didn't write the negative on the paper, but the words indicated the problem had a negative value. So on BC4, there's a couple more parts to it. There's a couple of questions on part 5 that we would encourage you to check out, some really good problems. And we're not going to do BC6, but I want to point out there's a couple things that are in here, so that when you try these problems later, you kind of know what you're getting into. So BC6 is starting the stem of the polynomial, right? There's no guarantee that if we see Euler's method on this year's exam, that the initial problem is going to be talking about differential equations, right? If we see a differential equation on the exam, that might be a head-to-head. We might do Euler's method here, right? But what if the problem started with just some Taylor polynomial? So you kind of start in part A about making a Taylor polynomial. This would be a really good practice to review what Tony and I did on Monday as well as the last week or so. But then all of a sudden in part B of this question, the same Taylor polynomial, now we introduce this idea of Euler's method because we're doing this Taylor polynomial with this function g. But then in part B, we introduce a new function f and a differential equation. And to do Euler's method, we have to know what that derivative value is. Well, notice our derivative of f is somehow connected to the derivatives of g, right? So g is generating this Taylor polynomial. So now we're going to make some really cool connections between developing Taylor polynomials and Euler's method with derivatives. So definitely try that one out and then compare your solutions with what we see in the drop box later on. So lots of good problems in there. Try them, right? Practice these problems because they're going to really test your true conceptual understanding of what's happening here, right? So thank you so much. We're so glad that you're here. And Tony, I think you have some tweets for us today, don't you?
I do. They're still coming in, and we don't want them to stop. So if you have a teacher that you really want to recognize, make sure that you tweet out AP Teachers Rock, that hashtag, and we're going to recognize Mr. Gilson. So please shout out Mr. Gilson from Central High, my Calculus AP teacher from last year. His teaching style is unmatched in terms of efficiency. He made me love Calculus' favorite teacher of all of high school. Congratulations, Mr. Gilson. And for our AP Students Rock hashtag, we are now going to recognize this group of students. I want to give a shout out to all of my AP Calculus BC students. They're all studying and working together to prepare for the examinations despite these challenges. And we hope that all the students around, the United States, our friends with North Canada, outside of North America, feeling the same way. And as always, if you're having trouble from a technological standpoint, if you are not able to access the internet, or if you have friends who are in that situation, or they just don't have the hardware devices that they feel they can be successful when May 12th comes around, please have them reach out to College Board, cb.org/tech, and they'll definitely take care of whatever issues that you or them might have. So great show today, Brian. I'm really excited. I'm already excited about tomorrow's show, Thursday. The topic is going to be logistic differential equations. You've heard a lot of things about flattening the curve. We're not going to tie this into what's going around us because that's probably pretty cliche. It's something that maybe you've talked about if you've seen it on the news. But we're going to talk about a lot of logistic differential equations that can apply to various populations, various spreads of diseases in general. So definitely look forward to that. But we're going to infuse and embed some previous ideas into those as well. So with that, Brian and I, we are out, and we certainly look forward for tomorrow. And we want all of you to have a great day. And as always, stay safe, stay healthy, keep learning.
Thank you so much, Tony. And if you didn't notice Tony's background, he changed it on me, and I think Tony, anybody at home figured out. It's kind of obvious to me now that I see the Kevin Costner in the background. So I'm going to go with is that my Dancing with Wolves? Is that my?
It is Tatanka, Lieutenant John Dunbar, my favorite movie of all time. Special shout out for those of you that are in the plains. Beautiful country there, South Dakota and Wyoming. So you're very blessed.
Kudos to anybody that figured that out, especially on Tony's first background. So Anthony G is going to take us out as always with our outro AP Calculus song.
All right, take care, guys.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus. Data polynomials. Infinite series. Differential equation. Calculus. Data polynomials. Infinite series.
And welcome to AP Calculus BC Live on this beautiful Thursday morning. We have a riveting lesson for you today over logistic differential equations, and we certainly want to thank all of you, the teachers out there, the students out there, for your basically your overwhelming amount of support for us, because we're kind of over the halfway point here for these videos, and I tell you what, it's been tough sometimes. Brian and I, we spend some time in the mornings trying to get these finalized, and then of course we have our own classes that we teach through the rest of the morning, through the afternoons, and then a lot of evenings we actually do some more training for teachers around the country, and then all of a sudden we find, hey, we got to get things really ready to go for our next morning AP Live session. So we kind of repeat that cycle again, and it's like becomes this really precious commodity sometimes. So trust me when I say we will never get tired of hearing from you through all the different channels of social media, whether it's Twitter or Facebook, and I'll tell you what, Brian and I were a little bit more cool, or if we were a little bit more go, you can hit us up on our Instas, but we just don't have Instas, but I think our dogs might. I don't know, maybe. Once again, if you want to grab the materials that are associated with any of our videos, you can find them in the description below each of the videos and print those out. And we certainly encourage you to work them with us. And then the problems that we don't do, you could work on those on your own. And some of you work those as part of your own e-learning in your virtual classrooms with your own teacher. Once again, my name is Tony Record, teacher from Avon High School, and I'm joined with my great friend and esteemed colleague and best question writer in the universe, Brian Password. Brian, how are you doing this morning?
You know, Tony, I'm doing pretty good, although I felt a little bit bad because yesterday we had this lesson on Euler's method. I hope everyone got to see it. And it was really difficult, right? Because it happened to be yesterday Euler's actual birthday. So we had Euler's method on his birthday. And a lot of people noticed that, except for you and I. I don't know how this happened, but we didn't even think about that, mention it, or anything. And so we got a lot of emails and tweets and people, posting on Facebook and sending us messages, text messages, letting us know we missed a golden opportunity. And I felt really, really bad about it. And so I was trying to figure out how could I atone, right, for my omission. And so at first I thought, he's number 4 on my all-time top 50 list, which I know that you like to keep my top stuff updated. You get my weekly blog about my top 50 people. And I thought maybe I could move him to number 3, kind of honorary, push him up one spot, but he wouldn't want that. I knew he wouldn't want that. He would want to earn that. Maybe one day he will earn that. So instead, I thought, I'm going to atone for my mistakes. So I'm going to make my background today in honor of my friend and your friend, Mr. Euler. And so here he is in the background, looking fondly at his Euler equation, the e to the I pi plus 1 equals 0, which is really, in my opinion, the most beautiful and poetic equation in all mathematics as it relates to the 5 most commonly used numbers in all mathematics. So one beautiful equation. And I know that a lot of teachers are amiss and a little bit sad this year because usually in Calc we're able to discover this equation and prove it or verify it using Taylor series and power series manipulations. So I'm going to do that because those topics are no longer tested on this year's exam, and we don't quite have the same amount of class time as we normally do. So I feel like I've atoned for my mistake. I said Mr. Euler is okay with me now. I've already written his family formal apology letter. But really, I'm more concerned, Tony, about what you're going to be doing because I don't see you changing your background.
Well, I don't have a background change, that's true. But last night I did go to my kitchen and I baked it from Mr. Euler. And I searched far and wide for 313 candles and we lit them. And we had our little celebration. However, we never got to eat the cake because shortly thereafter it turned into just a soupy pile of sweet goo. But hey, it was the thought that counts. So we did celebrate.
Is that why the fire department was at your house last night?
Yeah, you heard the sirens, didn't you?
Yeah, we did. Okay.
So anyhow, Mr. Euler, we do apologize and we won't forget you next year. So what we've got going on today, obviously logistic differential equations. We're going to talk a little bit about the arc length tomorrow, as you can see here in our schedule. Kind of relating that a little bit back to the rectangular world. But remember, as we said yesterday and the day before, a lot of these topics, or all of these topics for the most part, are going to fuse in some of the material that we talked about on the previous days, the days before, et cetera, et cetera. So again, don't look at the schedule and think, arc length, I'm good with that. There's still a lot of rich content, I think, that you can still glean some information from that will help you on your AP exam. And of course, next week we start our connecting AB to BC series with limits and continuity on Monday. So you definitely want to stick around for that. As always, we're going to show you the slide. It's probably a pretty important slide. You want to make sure that you're very geared towards May 12th as being the day that you'll take your AP exam. The fact that there are going to be 2 free response questions, and that's kind of the name of the game right now. We're going to expose you to a lot of free response questions. So we'll go into a lot more detail about the makeup of the exam as we draw a little bit closer. But as far as today's lesson is concerned, if you've got the printout in front of you, this is going to be the opening page. It's a really powerful page in the fact that the items in that right side, that what you need to know, are going to be referenced throughout this video time and time again. So you don't want to feel bad if we say, if you are taking the limit as t approaches infinity of your dependent variable, we know that that's always L. That's always this thing that we call sometimes the carrying capacity. That information is outlined here, and we want to make sure that you keep this handy throughout this video, throughout the time that you're solving these problems. On this year's exam, there's nothing wrong if you have this document printed out. You can have it along with you as you're taking the test. But just to summarize just a few things, the typical logistic curve might look something like what you see here on the left side of the screen. And the thing is, it's very often the case that we won't know what that curve looks like. We're typically going to be given its differential equation form, and it's a form that I'm not going to say that we can't solve it. You probably have the tools to solve it. The AP exam will typically never ask you to solve it because of the complications that involve the partial fraction decomp. It's like we have bigger fish to fry, basically. But the curve would look a little bit something like this, and it's some type of a curve that you may have been seeing in the news quite a bit lately. It could have a second branch to it depending on where the initial condition is. But remember, we're talking about the curves that solve these differential equations as being functions. So these would never really simultaneously exist. They would kind of depend on what their particular initial condition were. But the top line here is the one that you're going to really see us refer to a lot here through the beginning of the video. That's the basic form of this differential equation in logistic form. And one form has sort of a different factor version than the other form. And like I said, we're going to make reference to that here in a bit. So yes, definitely keep this handy as we're going to reference these items as we move through. We're going to start with some quick checks, which is going to serve as our warm-up. And Brian, I think you're going to take us through those.
Yeah, absolutely, Tony. And I want to make sure that we understand, and the students understand, kind of why we put these last 2 topics together between doing Euler's method yesterday, right, and then we're doing logistic curves today, because both of them rely heavily on this idea of being given a derivative, right? You have a derivative. There's a reason why there's an entire course in college called differential equations, because in the real world, there's so many situations where we can find or model the rates of change, but we don't know sort of the big picture in terms of what the original function would be, right? And so with Euler's method yesterday, we were given differential equations, particularly the ones that maybe we couldn't solve with our current tools. And then today with logistic growth, it's kind of a similar idea that we're going to be given for the most part differential equations, and then we're making these connections, right? AP Calc is all about making connections between what you're given and then something else. So how can we make connections between the different types of differential equations we have versus characteristics and traits on those solution curves? And so like I mentioned, you're not going to be asked to solve one of these differential equations on the AP exam. And you're not even going to be required to know the general form of the solution curve, right? But what they want you to be able to do is, given a logistic situation or differential equation, how can we glean information? What numbers in these formulas are important? Number 1, how do we even identify if it is logistic? And then number 2, what numbers in there kind of correspond to those important parts on that table that Tony shared a second ago in terms of the carrying capacity, the halfway point where it's growing the fastest, and then when it's concave up, all those kind of ideas. We could figure those out without ever seeing the curve, like Tony mentioned. So our quick check is going to give us 3 quick problems to see if we can solidify what Tony shared in that table. And so you might need to sort of screenshot that table, print that table out, and have it handy during today's lesson. If you haven't done this for a while, you kind of keep reference for it. We're going to keep coming back to that. So the number of students at Speedway High School, that's my high school by the way, that have heard a rumor at time t hours is increasing according to a logistic differential equation, which the following could be the differential equation, right? So in this case, they kind of gave us a hint that it was logistic by saying the word logistic in the problem, right? So a lot of times the AP exam will clarify that this is a logistic situation. So now we're figuring out which one of these could be logistic. So what's important to realize is logistic differential equations, as we solve in the solution curve, they start out exponential, right? We see that exponential growth in the beginning, and then when you get halfway to the carrying capacity, halfway to the limit, it sort of bends the graph and it becomes more of a log type of shape. And so they always start out exponential and they kind of bend as it grows toward the carrying capacity. And because of that, the equations will only have variables that are with respect to the or the dependent variable, right? S, kind of our y variable. And so the differential equation is dependent solely on those s values. The same way that when we do exponential growth, the differential equation is dependent upon the y values at that moment, right? And so we know if you see things that are in terms of x or t, whatever these independent values are in the denominator, that can't possibly be logistic growth. So we have to only have s or y in our formula. So I'm not going to eliminate a and c, and we're now down to b and d. B, this is just an example actually of exponential growth. This is unbounded exponential growth where it's in terms of y, k times y, some constant times y. Now we exponential growth, the solution curve will look kind of like this, whereas d now is one of those forms that Tony shared, right? So it's important to realize there's not just going to be one s. You're going to have, like Tony shared in that last table, a y out in front times something in that parentheses inside of that factor that would include a y expression as well. So d is going to be the only one here that is going to be a logistic differential equation. So we're going to use that now and see if we can apply it to a couple of examples. So this is the correct answer, that ds over dt is this formula. this one of those two forms that Tony showed, is that for this situation, what rate, right, we're asking for a rate, always highlight the information there, is the rumor spreading when it's spreading the fastest, right? So I'm going to sort of sketch, we know the solution curve for one of these logistic growth problems is going to look kind of like this, right, where we have this carrying capacity at the top here, and this is the carrying capacity. It's always important, everything comes back to that value, but then we also know from that table that when we're halfway up, right, when this y value is half of the carrying capacity, then that's the moment when it's going to be growing the fastest. That's the moment when this solution curve has a point of inflection where it changes from increasing at an increasing rate to increasing at a decreasing rate. And so if we can figure out the carrying capacity, then we'll know what this point right there is going to be as well. And so knowing our forms, this is the form where we have a constant minus our y value. So this value right here happens to be our carrying capacity. So we know the carrying capacity in this case is going to be just 500, which means this is growing the fastest. When is it growing the fastest? Well, it's always going to be growing the fastest when we're halfway to that carrying capacity. So it's going to be growing the fastest when s, which is our y coordinate, is half of 500, or in this case 250. Now we have to be really careful about the wording of the question, because the question didn't say when is it growing the fastest. It said what is the rate at that moment, right? So we know that s is 250. To find the actual rate that it's growing, we're going to have to take that value and then plug it back into our differential equation, as the differential equation is in fact the rate. So we're going to get 0.002 times s, which is 250, and then times the quantity 500 minus s, or 250. Now on an AP exam, on a free response problem, we can certainly leave our answer like that. And I would probably recommend that you would. There's no advantage on FRQ to simplify your numerical answers. But if you have a classroom teacher like me or Tony, we typically during the year like our kids to simplify, because in college, your professors are most likely to simplify these problems. And so if we simplify this 0.002, that seems to be a 1 over 500, that's 1 500, and then times 250 times another 250, and then doing a little bit of reducing here is going to give me 125. So the rate is going to be 125, and the units in this case was just going to be students per hour. I got those units from the original problem in the STEM. It told us that s was students and time was in hours. And so it's growing the fastest when 250 students have heard the rumor, when half the students have heard it. That's when it's going to be growing the fastest, and then the actual rate at that moment is 125 students per hour. Moving on to quick check number 3, same exact differential equation. Let's see if we can't sketch here a slope field, or sketch a solution curve in a slope field through the given points. So let's say if we knew that at 1 hour, when t is 1, 100 students have heard the rumor, we're going to have a little point right there indicating our solution curve, and then we're trying to sketch a solution curve. It's sometimes difficult. Students sometimes have a hard time with these knowing how to sketch them. And I tell them, if you go really slow on the slope field, you're probably overthinking it. I always imagine those little slopes on the slope fields are like currents or water. You're in the ocean, the current kind of just sit there and let it, kind of float in the ocean. The currents and the tides will kind of move you around automatically, kind of just go with it. So I kind of just follow these slopes and imagine they're kind of currents in the water. This is an ocean or a river, and you kind of see the flow of the water. Just follow the flow of the water, and you're going to get a solution curve that looks something like that. And we can see that as we get up to the top here, these slopes are starting to flatten out because we have our carrying capacity up here, which happens to be 500. And so this is the actual solution curve. It's a little bit different scales. It's not going to be quite the same sizing, but you probably didn't notice this. But the very first curve that Tony showed on that front slide was the solution curve to this problem. So this problem is a realistic, real world situation, and the real solution would look something like this curve here in blue on the bottom. It would be an example where it would be the bottom part of the curve, because we are definitely growing. You can't have more students. You can't start off with more students than you have in your school having heard a rumor at your school. So that'll give us a little bit of a quick check. Those are the fundamentals, I would call them, the main ideas, connect some ideas together. But we want to look again, more importantly, at some AP style problems specifically for the 2020 exam. And Tony has a really great one to start off with today.
Yeah, I do. I think we have got it's sort of a semi-traditional, semi-non-traditional kind of problem that we're going to lead off with here. But let's take a look. It says consider the logistic differential equation dy over dt is 1/2 y quantity 1 minus y over k. Now that's pretty traditional, right? We have this differential equation that mimics the form that we see on that first page. Now I do want to warn you a little bit. Teachers sometimes can be a little diabolical, right? Teachers know what I'm talking about. And you can see in this particular case that the usage of k is taking on a very different meaning. So we want to make sure that we're very clear with that. You never ever, and not just calculus, but any mathematics course, you just don't want to blindly memorize formulas and just kind of envision those letters that you would see in that particular formula from that particular book, because they might change. One book might use different letters of the alphabet to do things. Now in this denominator of this sort of this quantity, when we have a 1 minus dependent variable y over a value form, we want to think of that as that limit. Sometimes we call it the carrying capacity. Any of you that take AP Bio are probably very familiar with that word. We typically will refer to it more as the limit. And that value, if I'm not mistaken, on that opening page was called capital L. What a great letter to use for limit, right? But yet out in front, we had this other coefficient value that I believe called k. It's just like this constant that's associated with that particular growth model. As you can see, we kind of switched gears a little bit and we called that limit k, and now you have a known constant in front. So you want to be very careful with that. And in this particular problem, it goes on to say that carrying capacity, that limit, that upper ceiling, is somewhere between 4 and 20. We don't know exactly where, but we know it does lie between 4 and 20 exclusively. Y equal f of t would be the particular solution to this differential equation, and the initial condition is f of 0 is 2. So our part A is a very conceptually oriented question. It just simply asks, hey, in terms of k, for what values of y would f of t be increasing at a decreasing rate? So there's a little bit of interpretive nature that is going to be associated with this problem with this phrase. What the heck does increasing at a decreasing rate mean? Maybe you've heard that phrase. Maybe that came back, it reminds you back in the AD part of your curriculum. Obviously, there's many ways of a graph can increase, right? Concave up, concave down, linearly. But if we increase at a decreasing rate, what that's saying is that the curve is getting larger in y values, but it's not doing it as fast. So we want to associate this phrase with essentially con down, right? That's perfectly acceptable. That means concave down. Okay, so now we start to think, all right, now what does this logistic curve look like? Well, you've seen a couple of models of one so far, right? From the intro to the lesson in Ryan's quick chat. But maybe the curve might look a little something like this, right? And as I said before, we don't know what the ceiling is, right? Now the ceiling is normally called L, but in this problem we're calling it K. And that K is just something between 4 and 20, as we can see in the stem of the problem. What we want to be concerned with is where in this picture do you see this blue shape, right? If I were to kind of grab this shape and move it over, where would I see that happening? And as we can see, it would occur on the latter portion of the graph, if we want to call it the portion that occurs after this interesting point right here and then beyond. And that point right there is a point of inflection. You can see that concavity changes, but that point of inflection has a very important meaning, as we've been sharing with you. That point of inflection is going to be reached when we are at half of that carrying capacity. That carrying capacity or limit is called K. So half of that K would be K over 2, of course. And we know that we're never going to get any higher than this K. And so we can stop right there. Now I'm going to define my concavity over this open interval. I think it makes a lot of sense that K needs to be open. We're not going to fight the fight about do we include the K over 2 or exclude it. It's going to be fine in this case either way. But the K over 2 to K that's the interval. That's the values of K that we want to use to depict this increasing and decreasing rate in this problem. Now I do have a technology component to this problem. For those of you that might use a TI Inspire, this is something that you can easily program into your calculator. You can also do this very easily on Desmos, and I even believe GeoGebra has a nice slider tool. But basically what I've done is I've replicated that particular differential equation, and I'm allowing my K to change from the 4 to the 20 that we know that he's going to take on those values. And as you can see in red, I have the ceiling K equal 4 at that point. And if I slide this, if I just let this grow, what I want you to do is to keep careful notice of the value of this order pair, the value of this point of inflection, particularly the Y value. The X value doesn't really matter a whole lot right now, but that Y value has a relationship with this K, and it's probably pretty easy to see what it is, right? 14.7, I'm sure you see it at this point. And I can take that all the way up to my highest K, which would be 20. And again, we've retained that relationship of the Y value here at the point of inflection being half of the carrying capacity. If we move on to part B, I'm going to just briefly introduce what's happening in part B, but we're going to assign this one for homework tonight. And you're asked to find the second derivative of this differential differential equation in terms of k and y. Certainly has a lot more to do with the portion of the course. Knowing chain rule would be good. Knowing implicit differentiation would be even better. But problems like this have shown up in the past on the AP exam. It takes me back to the baby bird problem. Teachers, you know what I'm talking about. Students, you may have solved that in your class. But it's a very poignant way to have the students exercise their ability to know implicit differentiation. And there's all sorts of questions that can be asked based on the result of that second derivative. So definitely try that problem. You can check it in the solutions when they're released later on. But I do want to go ahead and turn our attention to part C. Part C asks to find the limit as t approaches infinity of 2t plus f of t over the inverse tangent of t plus 5 times t. Now, with many limit problems like this, it's likely, especially if you're a pretty seasoned calculus student, you're kind of on the scene and you probably have a pretty good idea that maybe this is going to use L'Hopital's rule, but you want to be careful because just because you see a limit in BC calculus doesn't mean it has to be L'Hopital's rule. So what we're going to do with this problem is just kind of exercise some caution. And how about we take this limit and just decide to do so separately? Maybe we just focus on the numerator only, and then we can focus on the denominator in a separate limit altogether. And the reason why I like this approach is in the event that maybe this does require L'Hopital's rule, we're setting the stage to present that in the best possible manner. We'll talk about that in a second. So what is the limit of this numerator? Well, if we try to plug infinity in for t, right? If we allow t to take on that really large t value, we can see right from the very beginning we have 2 times a large number, which is going to output a very large number. So I don't like to use an equal in this case because we're not really showing equivalence to something that's in numeric. So maybe I'll say this leads to 2 times infinity, which is infinity. Now, it may not really matter a lot what f of t is here, but I do want to talk about it. F of t is the solution of this differential equation, right? It's a curve that very likely is going to look like this. You'll probably see this a lot on these slides. And as this t gets really, really large, I think that f of t is going to close in on some kind of ceiling value, right? And we've already established that guy is going to be k. It's somewhere between 4 and 20. Oh, okay, well, so k is a constant. So we can see that this is just going to become that infinity. Okay, well, let's take a look at that denominator then. What is the limit of the inverse tangent of t as t approaches infinity? Now, this might be a good little blast from the past, a little lesson about, okay, well, what is the inverse tangent of infinity? Sometimes you see that it seems to show up a lot on improper integration problems. So the graph of inverse tangent, if we want to take it all the way back to trig class here, inverse tangent, arctan, if you want to write it as such, could look something like this. I'll just use t there. So it has a curve or an appearance that looks like that, which ironically kind of looks like a logistic curve, but it's completely something separate. But what we want to kind of isolate on here is the fact that there is a horizontal asymptote there, pi over 2. Right? Tangent has vertical asymptote pi over 2. Why wouldn't inverse tangent have a horizontal asymptote pi over 2? And it happens to have one negative pi over 2 as well. But we're concerned with what's happening on this side, right? As t gets really big, t gets bigger and bigger and bigger and bigger. Well, that y value is just going to cap out no higher than pi over 2. In fact, it'll never reach pi over 2, but we can say that it's certainly approaching pi over 2. So far, this is looking pretty good, right? This is looking pretty numeric. But as soon as we get to the 5 times t, we're going to get that infinity value again. So we can construe that we have an indeterminate form, right? Infinity divided by infinity. And what's nice about this is that we see that L'Hopital's rule does apply. We've sort of communicated that condition that needs to be met. So let's just go ahead and write out. We'll say that L'Hopital's rule applies. You can spell L'Hopital's rule a couple of different ways. I'll choose this way. So if L'Hopital's rule applies, what do we do about that? Well, we take this limit again as t approaches infinity, but now we have to take the derivative of the numerator and the derivative of the denominator, right? We're not using the quotient rule here. We're doing like f prime over g prime. So 2t's derivative is going to be 2, and the derivative of f is of course f prime of t. The derivative of inverse tangent might be one of those elusive derivatives. It's probably likely that you won't see that derivative very often on an AP exam, but it's awful good to know. It's awful good to have it in your back pocket. At least this year you may not have to memorize if you see it. So you have 1 over 1 plus t squared, and of course the derivative of 5t is 5. Now if we rethink our attitude about letting t approach infinity here, what we have is of course the constant 2, and then we add to that, and then we have to think, oh, okay, well what is this f prime of infinity, right? In other words, what is the f prime value going to approach when t gets really big? Well, once again, if we revisit our graph up here of f, right, this would be the solution curve f of t. The derivative of this f of t starts to get smaller and smaller and smaller the farther we go out, right? So that's that flattening of the curve that you've heard so much about in the news. So that's going to produce a value of 0 there. And then in the denominator, of course, if we let this t becomes infinity very large down here, we would end up with 1 over infinity, and we know that sort of zeroes out, right? That becomes a 0, it's very close to 0. And then when we add the constant 5, we can finish up with a very nice finite answer. 2/5 is the answer to our limit. So a lot of great things going on there in part C that pertain to a lot of AP ideas. And then I'm going to finish up BC1 with yet another limit here. It is known that this limit, as t approaches a of this numerator 2 of f of 1 over t minus a squared, all over 5e to the t squared minus at is equal to 4. Our job is to solve for k. Remember k is that ceiling somewhere between 4 and 20, let's hope, that now has to model or adhere to this particular limit. All right, so once again, if you're not sure, well, maybe this could be L'Hopital's rule, maybe it's not. We don't know yet per se. So it's perfectly suitable to go ahead and split this apart. So if we take the limit as t approaches a of the numerator, well, that means that we are going to try to directly substitute an a. With my students, I call that a green light. If you can substitute your chosen value of t in and get something numeric, you have a green light. Otherwise, you have a red light and you have to do a little bit more work. So if I let t be a minus a, well, okay, so far we're in the game, that's 0, or approaching 0, something very, very small. If you square that, you actually get smaller, right? When you're squaring something that's very, very small fractions or decimals close to 0, it gets even smaller. So I end up with 1 over something so incredibly small that this is kind of behaving like 2 times f of infinity per se, right? And then we have to think, okay, what is f of infinity? What is this solution curve? Whoops, the solution curve as t gets really big. Well, I told you I was going to keep drawing this over and over again because you can't see it enough. But the solution curve might look something like that. And yet, as we keep getting bigger and bigger, the value of our function is just going to approach x, right? As t gets bigger and bigger, the value of our function is going to approach our carrying capacity k. It's going to approach k. So this is going to become 2 times k over 2k. So I don't think L'Hopital's rule is going to apply here because we can't get an indeterminate form out of that. But nonetheless, we're going to go ahead and figure out this limit of the bottom. And this one is actually, I don't know, maybe even a little easier to follow because if you directly substitute here and allow this t to become infinity in this case, we end up with 5e to infinity squared minus a times infinity. We end up getting, how about I approach a? I was like, hey, t is not approaching infinity, right? T is approaching a. So if we let the t swap out and become an a, we end up with a squared minus a times a. A squared minus a, that's 0, right? So 5e to the 0, of course, is going to be 5. So it turns out that this limit is not indeterminate by any means, and we can say that we end up with 2k over 5 when we piece this back together. But yet we're told that the result is going to be 4. Right? So that's just one way to organize it. You can organize this a variety of ways, of course. But once you solve this, it's pretty academic at this point. That 2k is 20, and that k value is 10, which is a good thing because it did lie between 4 and 20. So the stem of the problem is preserved, and we have a solution that does make sense in the context of that stem. So there's your BC1. I think we're going to switch over to BC2, which has some very interesting components. Didn't Brian? I think you're going to take over there, right?
Yeah, absolutely. Thanks, Tony. So I hope that you guys are seeing through these examples that it's not just about knowing logistic growth, right? It's knowing how we can connect these properties back and forth, and then realizing on our AP exam, this is true any year, right? You wouldn't see on any year, most likely, one FRQ that decides or talks only about logistic growth. There might be one part of an FRQ. So what we're trying to do in these situations is give you opportunities to make some connections between these different properties of the solution curves and the differential equations by also making a lot of connections to other topics of BC and from AP. Because on this year's exam, like any year, this year in particular, you're going to be able to go back and forth like that. So you might have a L'Hopital's question or another question in the middle of something else that you're doing, right? So BC number 2 says the number of students S in thousands. Notice the units are pretty important here. We're going to play a big role. The number of students in thousands that have uploaded their calculus BC exams after T minutes when the portal opens. This question is pretty timely because we're going to be doing this right here in just a few short weeks. Satisfies the logistic differential equation S over 8 times the quantity 125 minus S. And no students, hopefully, have uploaded their exams at the moment the online portal opens. So this is going to give a nice little model, hopefully, for what we're going to see this year. And I tried to write this problem so that way if we did solve it out, it would look kind of similar to what we might see on a typical year. Because we have about 125,000 BC students that might take the exams. So find the maximum rate. So it's one of those maximum rate problems again, that the exams are being uploaded into the portal. So I'm going to go this problem a little bit quickly because we saw this on our quick check as well, right? We know that our maximum rate is going to occur when we're halfway to the carrying capacity. So if we just figure out what the carrying capacity is, then we can start working from there. Well, this is in one of those forms that's already in logistic growth. We want to make sure our equations are in the correct form. This is in that form, meaning we can identify L. Sometimes you might have to manipulate the form a little bit first, and Tony's going to show us an example of that here on the next problem. But in this case, this S in front times a constant, and then another constant minus S is one of those two logistic forms. So we can quickly see that L is just 125, meaning that the carrying capacity, the most students over time that could upload this exam would be 125,000, right? So S is in thousands. So that means the maximum rate is going to occur when L, not L, but S is half of that, right? When S is half 125, or you could call it 62.5. It might be better for us to leave it in terms of a fraction in this case. And so this is when it happens in terms of the number of students. We don't know the time that it happens, but we know when the number of students is 62,500 is growing the fastest, but it wants to know the actual rate. So just like before, we have to plug that value in there. So we want to find this when S is 62.5 or 125 over 2. We're going to get 125 over 2 times 80, or 1 over 80 from our differential equation, and then 125 minus 125 over 2, or 62.5. Because it's a little bit early this morning, I want us to get to some more problems that are more exciting. I'm going to leave this one unsimplified, but on the exam, of course, you're always allowed to leave it like that. So we can find out what the maximum rate growth is by evaluating that expression. So I want to look at on this problem on BC number 2, just one more part of it, because it's going to tie in to what we did yesterday. So I want to make sure we're making these connections and still remembering how to do these older topics and tying all these things together during these next several weeks. And so I'm skipping part B, but I put part B on the slide so you can see what the question was. And I put it there not just so you can see it, but because I started to get my table ready and realized, wait a minute, I can't solve part C. We needed the answer from part B to help us. Okay, so same problem, but we're going to use Euler's method with two steps of equal size, starting at t equals 1. That's going to be important, starting at t equals 1 to approximate S of 3. And so I have my table pre-made for us here. So we're starting at t equals 1 and not t equals 0. And we're doing two steps of equal size. That means each step is size of 1 because we're trying to get to 3. And then that means I have to my starting value S of 1 in this case. The stem of the problem told us S of 0, but we actually need S of 1. And we don't know that. But in part B, we gave you that information. It says at 1 minute, 40 students have uploaded their exams online. So that's telling us S at 1. But you got to be really careful on the problem because if you plug 40 in here, you're going to get some really crazy numbers because remember, S is in thousands. And so if I plug 40 in there, I'm not saying there's 40 students. I'm claiming there's 40,000 students, which is not the case. So we have to remember the actual S value. If 40 students have taken the exam, that means it's 40 divided by that in terms of S, right? So that's going to be 4 over 100, or in this case, 1 over 25. So it turns out S value is only 100 or 1 over 25 or 0.04. So be careful with the units on that problem. To be honest with you, I don't think the AP exam is going to try to trick you up with a unit question like that. That's not their intention, is to fool you. I'm a little more diabolical than they are, so I just want to make sure we're paying attention to units. And so once we have this, then we can create our Euler's formula, right? Remember, the next y term is always your current y term times or plus the step size times the derivative of our current point. In this case, x is going to be t and y is going to be s. And so if I want to know s sub 1, the next term of the sequence, it's going to be my current y value of 0.04 plus a step size of 1. And then I have to plug in my information for my point into my differential equation. And notice our differential equation only has s values in there. So we're not going to actually plug any t values in because we don't need to. There's no t values there. And so our current s value is going to be 0.04 over 80 times the quantity 125 minus 0.04. And whatever that is, that's going to be our s of 1. I'm going to call that value a. So I'm going to try to write all of that down. I want to get my calculator right now on the air and simplify that. But we could reduce and simplify that properly, I hope. And then once we have that, then we're able to find our final s value. Because it's going to be whatever our a value was plus, again, step size of 1 times the derivative, which is just going to be this equation. Remember, our current s value is just going to be a. So whatever that a value was over 80 times 125 minus that a value. So if we had plugged a number in there, this would have been our approximation for the number of students that have taken the exam at t equals 3 minutes using Euler's method. So it'd be kind of neat because to finish this problem out, find out the a value and solve it, and then also do part B with a tangent line approximation for the same thing, so we can compare how those two problems sort of relate in terms of their answers to each other. So I know we're running a little bit short on time, so I'm going to not do part B, but it's in good connection to Riemann sums. So just like we saw in one of the problems yesterday, we're going to estimate S of 3 again a third time. So we're trying to approximate this, how many students have uploaded their exams after 3 minutes during that portal system. 3 different ways. We use a tangent line to do it, then we're going to end up using a Euler method to do it, and then we're going to do Riemann sum to do the same thing here. So then Tony is going to lead us through another example that I think will be a good one here. And we probably don't have time to do all these examples, but maybe we can get through 1 or 2 of these final 2 problems.
I agree. I think I'll talk through A very quickly here and then just maybe introduce B and then hand that back over to Brian to look at the end of this particular document. But in this particular problem, we're going to consider a differential equation defined as dy dt 3 over 20 times y times this elusive g of y portion. And of course, as always, y equal f of t is the particular solution. Now, I've written the main form of our differential equation that we see on the front page, right? Now we're using L as that limit or that carrying capacity. And in part A, we're defining g of y to be 2 minus y over 1200. You'll see a lot of times in these problems that have been written is that we allow for that function piece here to change throughout the parts of the problem and invoke some different kinds of mathematics that you would have to use to solve. This particular problem is asking you to solve the limit t approaches infinity of f of t. So one of the first things that we want you to be really confident with is to look at that and say, oh, that's just how high will that function f of t go, the solution curve go when t gets really big. And that's the definition of that limit, that carrying capacity. So this is really one and the same with L. Okay, well now let's reassemble this differential equation. Let's write the very specific one to this part. So we would say that the dy dt is 3 over 20 times y, and then the g of y takes over as 2 minus y over 1200. So it certainly has the essence of that differential equation, but it's just not quite in the right form. It's pretty obvious that some students might want to gravitate towards 1200 as the answer. You could bet that if this is a multiple choice problem, 1200 would be a destructive choice. Maybe 20 would be a destructive choice as well. But what we have to do is perform the mathematics, perform the algebra that will cause that 2 to become a 1. And once you do that, you now have form that you want. And that's just factoring. I want to say simple factoring, but there's a little bit of a twist to it, as you're going to see. So if you bring that 2 out in front, we're going to see a little bit of reduction 2 over the 20. We could call that 3/10 if you'd like. And then of course the 2 would become a 1. But now you have to think about what this new denominator is going to be. And it's not going to be 600, which by the way would be another great destructive choice, I believe, wouldn't it, right? So you have to think about what do we do with this 1200? And because of this value being located in the denominator, you just do the opposite. Instead of dividing a value by 2 because it's being factored out, you would have to multiply. And of course, it's very easy if you wanted to maybe distribute that 3/10 back through and perform the mathematics to see if it does match the original result. And in this case, it certainly would. And by that time, you can see, oh, that is that limit, that is that carrying capacity. So our answer would be 2400. Okay. Part B is asking something kind of similar. You obviously have a different function that you have to assemble when you use the 4000 minus 4y. But now they ask you to find the y value when f of t is increasing at its greatest rate. So the student would have to infer or look into this and see that we're talking about increasing at the greatest rate is happening at that point of inflection. And again, that's one of the items that's discussed on the front part of the sheet. So we're talking about this point of inflection here, which we know to be half of that carrying capacity. So you would still have to do essentially the same thing that we did with part A, but just remember to take half of that limit. So I definitely want you to try B. It won't take you very long, but that will really put sort of the capstone on your ability to manipulate these equations and understand the difference between the L value and what it means and the L over 2 value. And I think Brian's going to kind of paraphrase some of these other ones and then just kind of maybe jump to the finale here.
Sure. And Tony, real quick, wouldn't you agree that the hardest part about this is when we come up with these problems and write them, they kind of become like our babies in the sense of we love them so much, it just kills us to not do every example. Like having to pick and choose which ones we get during the sessions is really kind of brutal because we think we have this plan every day. Here's all the problems we're going to cover. And then literally every day, we've never gotten through all the problems. We always underestimate how rich these problems are and how long they're going to take us to get through on the air. But it's always a sad thing. And so Tony and I love these problems. We love the connections that they make. So we really do hope that you're taking these documents off the Dropbox link that Tony shared at the beginning and then doing the extra problems because it does give you so many opportunities to connect concepts together and then truly develop a conceptual understanding of what's happening. And if you do those things, Tony and I are really confident that you're going to be well prepared for this year's AP exam. So on part C of this problem, we're not going to work this problem out, but you're never going to have to on the exam solve a logistic differential equation, right? You can solve them by partial fractions. The algebra's pretty ugly. You're not going to have to. But part C gives you an opportunity, right? Develop one you can because it kind of takes out some of the ugliness for you and let you practice that partial fraction integration technique in a little bit cleaner way. So it might be worth trying to solve for part C, but check the solution because you don't have to get y by itself for this one. It doesn't say find the solution y equals. It says find an expression for y. So once you solve it, don't try to solve for y and gather all those terms up. Just get the solution, find C, and then you can stop there and you can see our sample solution to see where we would have stopped. Okay. Part D, I really do want to mention this quickly. I want to do it briefly because I want to tie in another Taylor polynomial problem in case you haven't had a lot of practice with those and make sure you realize they up here anywhere on the exam. And so D is in fact another situation, right, where g of y is 240 minus 20y, and then I went ahead and plugged it in there. There's my g of y, and I put it into our differential equation right here. And this is not in that proper form. So Tony kind of showed us we can't tell what the carrying capacity is right now. I like to put our logistic problems sort of the standard form. By putting it in standard form in this case, the best method will probably be maybe to just factor out a 20 in that parentheses. And so it's kind of nice that if I factor out 20, it cancels with the 20 in the denominator out front. And we end up just getting something like this. And so now that we're in proper form, we can make the connection that in this case we can identify that carrying capacity of 12, right? So we know that 12 is our carrying capacity. And then notice what we're doing here. We're trying to make a Taylor polynomial for a function called h, a whole new function, right? Has no real connection to the other stuff except for the fact that the derivatives are connected in some way. And so the function h has derivatives at x equals 30 and h of 30 is negative 2. Find the second degree Taylor polynomial at 30 if the formula for the derivatives of h is given by this expression right here, which is connected to f, right? So that's the connection that we're going to make. I went ahead and I gave us the Taylor polynomial sort of generic form here, right, with our problem. So we have to come up with, we're going to write our Taylor polynomials for h at 30. Remember, our job is to figure out values for all those h expressions. So h of 30 in this case, well, luckily for us, the problem just told us that h of 30 is negative 2. So we know that one. But then finding h prime and h double prime, that's going to make us use our formula here. So if I want to find h prime of 30, that case is when n is 1. This is where the part that I want to make sure we're connecting because if n is 1, and I plug in our formula, then it's going to be f is going to be the zero derivative, right? N minus 1, 1 minus 1 is just going to be 0. So really, h prime of 30 is just negative f of 30 over 6. And this is a graph of f, right? This is our function f right here. So how are we going to find f of 30? Well, on this little problem, we label that halfway carrying capacity, no matter what L is, the t value, the time value there is always going to be 30. And so f of 30 is just this point right here, which is L over 2. And since we knew that L was 12 in this case, since we cleaned up our differential equation to find L as 12, then we know that f of 30 is going to be 6. And then negative 6 over 6 is just 1. So we made that connection to the carrying capacity and then brought it back to half the carrying capacity. And so we get negative 1 for h prime here. And we get something like this. And then to finish off, we have to find h double prime of 30. And using our nice little formula here, it's going to be f prime of 30 over 6. And so now not only do we have to know the y coordinate there on f, we now have to find f prime. But remember, our differential equation is f prime. So we can find f prime there pretty easily by, again, plugging in 6 for y, since that is our value right there. Our y coordinate is 6. We would end up getting negative 3 times 6 times 12 minus 6 over 6. And a little bit of reducing there gives us a negative 18. So if I change this up to a minus sign, we're going to get minus 18 and then the quantity x minus 30 squared over 2 factorial. So a good little connection to Taylor polynomials. We're not going to get to BC4, but man, I love this question. So make sure that you have a chance to get through it. It enters the table of values that are logistic, and it gives you a carrying capacity, and it goes through a lot of those connections that we talk about on this lesson about approximating a derivative and knowing which numbers pick. It didn't tell us where to approximate it. We have to try to deduce what the c value is from the information. So you definitely have to understand logistic growth graphs, the carrying capacity, and the half the carrying capacity to decide what number they actually wanting us to approximate. How can we find that on the table? So I'll be interested to see which ones you can figure that out. And then could A be 26? The table is a really neat problem. And then we kind of finish off this problem with another Euler method example, which I really love, and another Taylor polynomial. So I hope you'll find time to do those problems because I think they really build a lot of connection. So try those, check our solutions tonight, and let us know what you think about them because hopefully you're enjoying them as much as we do. But more importantly, everyone's favorite part of the show, we have tweets with Tony today. Tony, what do we have today?
All right, today's feature tweets for AP Teachers Rock. This one is a shout out to my AP Calculus teacher, Mrs. Fonador. I hope I pronounced that right. I apologize otherwise, but she always tries to instill a love of learning in her students and works hard to give individual feedback. So definitely an AP teacher that rocks. For AP Students Rock at Chieftain Nation, AP Calculus student. Shout out to you guys. Keep plugging on. AP Students Rock. This is from our good friend Valerie Sailor, who's a member of our community. I believe Brian has worked pretty closely. So wonderful job. Again, if you're having any trouble with technology or if you have friends that are having trouble with technology, please have them reach out to cp.org/tech. As we close today, seniors, faced with the reality that you're not going to return to school. It seems like this chapter is over. This chapter of your life is done. Brian and I talked about this a lot. It's not done. You have the ability to rewrite it. And what better way to rewrite this chapter than to rock in this AP Copy C exam and the rest of your exams? And you can do that by continuing to watch our videos, tuning in, work these problems, work with your teachers, and we will get you there. We promise that. So fun. We want you to stay safe, stay healthy, keep learning.
Yep, and join us tomorrow for ArcLink, connecting that to everything that we're going to do in the exam, and see if tomorrow is the first time ever Tony and I can make it in the 45-minute time slot that we were trying to make it each and every session. So I feel like tomorrow is the day, Tony. And as always, our good friend Anthony is going to take us out. Bye, guys.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus. Data polynomials. Infinite series. Differential equation. Calculus. Data polynomials. Infinite series. Differential equation.
Welcome everybody to this very special Friday edition of AP Calculus YouTube Live. We're going to be taking a look at the BC topic of arc length of a smooth planar curve. We are so glad that you are joining us today. As always, we have materials in our Dropbox. If you want to click on the link under the video, you can find a Dropbox folder that has the materials. And as our friend Ted Gott mentioned this morning, today is sort of like a breaking news kind of session because we had our materials planned. I found a few flaws in our materials, and so if you had downloaded these materials either yesterday or maybe even an hour ago, you might find a couple of differences in our lesson today. So it'll be the newest and greatest version uploaded in the Dropbox for you, and hopefully we won't find any or too many more issues with the problem. This happens when we do these lessons, and we try to create new and creative questions every single day. Is that sometimes we're kind of pushing the envelope for our ability to proof it and check these before we go live on the air. But we are glad that you're here with us today. Tony, how are we doing today?
We are fantastic. I'm excited to go here. In fact, I got my sunscreen because you told me that we were going to go on a hike, so I need to get my SPF 50 going here. So
Tony, I think you do not. So no, Tony, that was just a problem. We're doing a problem today. We're on a hike. We're not actually.
Oh,
we're on a hike. Okay. I've done that twice now. I'm gonna have to put some disclaimers on there just to say, hey, this is not, this is virtual versus reality. Right? I think we maybe been homebound a little bit too long.
I think that's probably it. I think that's it.
Well, regardless of the confusion, I hope that you're excited today. Had a great lesson. You got your happy mug going on the other side. It's a pretty nice looking mug there, and you got your virtual classroom back in the back of you. So I think we're geared up, ready to go. And so before we jump right into today's lesson, we want to share a couple of upcoming things. Well, obviously today we've got this idea of arc length. We also have in the BC curriculum normally this kind of arc length in terms of parametric functions, total distance traveled, rectilinear motion. On this year's exam, so there's some comparable ideas in parametric unit 9, but we'll be discussing just the items that are tested on this year's quantity exam only. So anything we talk about today is certainly going to be fair game on this year's test. And then looking at next week, we're going to be talking about connecting AB to BC topics because we know that a large percentage of the AP topics, or a large percentage of the BC exam is going to include AB topics. So all those things are really going to be important to us. And so we're going to be refreshing, reviewing those topics as well as making some connections to how those relate to some of the BC unique topics as well for this year's exam. About that, we're hoping you'll join us for those and continue into our AP prep. So as always, a quick reminder: the exam for you guys will be on May 12th. It's 2 p.m. Eastern time, but it'll be whatever that would be in your time zone. So if you're on the West Coast, Pacific time, you'll be taking the BC exam at 11 a.m. If our math is the next day would be on June 1st. We hope you'll be able to join us and join the most of the students taking on May 12th, if at all possible. And so without further ado, we are really excited to start the lesson because Tony's going to get us jump started on a couple of quick reminders about arc length as well as a couple of quick check problems to make sure that we're doing these problems correctly.
Certainly, Brian. Thank you very much. And really, the catalyst that makes this lesson go is this formula that you see right there in front of you. If you got your document, we have that on the opening page as well. And the preliminary information within this formula box says that we need to let the function y equal f of x represent a smooth curve on the interval from a to b. We're not going to go into a lot of detail about what does the word smooth mean, but for all intents and purposes, it means that our curve must be continuous. And then there's a little bit of extra caveat in that the derivatives must be continuous as well, especially that very first derivative because we use them so heavily within the context of this formula. Anyhow, the arc length formula at that point from some x value a to another x value b is defined as the integration from a to b of the square root of 1 plus f prime of x squared. The derivation of this is something that we're going to leave to you. It's probably something that you've already talked about in class, but it does have to do with the Pythagorean theorem. Maybe you remember back one of our very first videos. In fact, I want to say it was maybe Brian and his very first video, and into the second video, we talked about the parametric version of arc length and how it lended itself very well to using this as a sort of a springboard. Now we just have to worry about this particular formula in the rectangular world only. All right. So let's go ahead and warm up a little bit. Right. So let's do it. Right. Warm up with a little quick check. And what we have here is a very traditional arc length rectangular problem. All right. So we have the function f of x, which is the cosine of 3x. We are asked to write, but do not evaluate. Talk a little bit about that in a second. An integral expression that gives the arc length of f of x from 0 to pi over 3. So we're going to use, I think, L as our expression or variable, I should say, for arc length. It doesn't matter what you decide to call it. You decide to call it anything. We know that this is an application of definite integration. And to be honest, often it is the case that those boundaries are going to be provided for you. So you just read them right from the text of the problem. So 0 to 2 pi over 3. And then we have the square root of some stuff, right? Well, that stuff, obviously, if you kind of revert back here, has this f prime of x value in it. And we don't readily know the f prime of x within the problem. So somewhere off to the side, whether you do this at the very beginning or now, it's really up to you. But you are going to have to find the derivative of that. So be very careful here. The cosine 3x is a chain rule derivative, right? So we have the derivative of cosine, which we know is negative sine, but then the derivative of 3x is going to produce that extra little 3, is not. So we have negative 3 sine of 3x as our f prime. So if we move back to our structure of our arc length formula, we would now have our 1, have our plus sign within the square root, and then of course we need to square that f prime. Now whether you choose to do a little bit of that squaring is up to you. Let's say that I decide to square the negative 3. That's pretty easy. Positive 9. Maybe I decide to square the sine and call that sine squared. That is certainly one acceptable way to express that. And then if you throw your differential at the end. But you could have also just wrapped this negative 3 sine 3x all in parentheses and squared it there. But part of the reason why I squared this is to kind of indicate to you that there's a very good reason why many of these problems ask you to simply write do not evaluate, because that's not a very easy derivative, a very easy integral to tackle, and it would very likely require technology. And we do have a problem later on that Brian's going to share with you that will implement that idea of technology only because we want to let it sort of show a sort of a more interesting end result with that hiking example that we talked about. But by and large, with many of these arc problems, you might just be setting them up, especially this year. If we take a look at quick check number 2, then quick check number 2 says a portion of the function g of x is given above. The arc length of the function g of x over the interval 0 to 3 is given by this particular definite interval expression. Oh, well, that's interesting. We have the expression for the arc length. Let's see what they're asking us. The question is find g prime of x. So look at this. It's sort of like moving backwards, I guess, to explain it, in the simplest way possible. And it really forces the students to understand the inner workings of the formula. For example, we know that this portion here, that 4/9 x squared, that had to comprise that g prime of x squared. Remember, our function is g now. So that's one thing that we could document. We know that g prime of x, all quantity squared, is 4/9 x squared. And from that, our job is to figure out what just simply the g prime is. And you look at this a little bit, you think, okay, well, really all I have to do is take the square root of both sides, which is exactly right. But you got to be a little careful with this, because if we do take take the square root of both sides. I don't know if I said take the derivative or take the square. It's early. We want to take the square root of both sides. And if we do that, the square root of 4/9, of course, is 2/3. The square root of x squared is x under certain conditions, right? Because technically, I guess the answer would be the absolute value of this, right? Or maybe plus or minus, right? Whenever we take the square root of both sides of an equation, we have to consider both the positive and the negative answer. Well, we're not going to have both of those as our answer. We have to choose which one is correct, and we have to choose wisely. So if we look at what's going on, look at this graph of g of x. Take some sort of some mental notes here. We know that this function is, well, that function's above the x-axis. It's positive, but is that really the reason why we might choose to go with a positive result? It doesn't really have much to do with g of x being positive. We want to figure out what's the sign of g prime of x. And you can see as this function is increasing, it has derivatives all along the way that are going to be positive, right? The slopes of those tangent lines are positive. That's what's going to make your decision. That's what's going to dictate the fact that you're going to use only the plus version of this, and you have g prime be 2/3 x. Okay. Take a look at quick check 3 before I hand it over to my esteemed colleague Brian Passwater. Here we have a portion of the function h of x. The arc length of this function h of x over the interval 0 to 2 is defined here again by a very familiar looking expression, that arc length formula that we have now starting to get used to a bit. And now our directive is to find the equation of the tangent line to h of x at x equals 0. Well, so finding the equation of the tangent line, that's usually a pretty easy thing, right? Take that derivative of h, plug in this 0, we're off and running. But the problem is that h of x function isn't very readily known. But we can go to this arc length formula, extract that information out, and boom, there we have our h of x. So let's take a look here. So once again, the inner workings of this formula right right there is going to be our h prime of x squared. So we can document that. We know h prime of x squared is 2/3 e to the x over 3 squared. We forgot all that. All right. So now let's get our h prime. So our h prime of x is going to be found by taking the square root of both sides and paying very close attention to what our sign is going to be. So we can really get rid of the squared when we square root this expression over here. And then again, we're considering, I know I need a plus minus here under normal circumstances, but as I look at my h of x again, once again, we have another increasing curve, especially throughout this interval 0 to 2. That's where it really matters. And therefore, I'm going to go with the positive version. All right. So it looks like I've got an h prime. What better place to go than to find a slope? So we can figure out h prime of 0. This is going to be the slope of our line. So we have 2/3 times e to the 0, I believe, right? 2/3 e to the 0/3. So we have 2/3 times 1. And then really about the only thing I'm missing is the other part of that point, right? It's like we have half of this point. I just don't have the y coordinate, right? The h value that goes with that 0. So I have to figure out what h of 0 is. Okay, well, again, I don't really have an h function expressed sort of analytically, but we have maybe the next best thing, and that's the graph of h. And it's a very well-behaved graph of h, especially here at 0, in that you can extract that y value to be 2. All right, there's your vital information. You know that this is a y-intercept, so if you want to use the y equals mx plus b version of the equation of a tangent line or a line in general, it works perfectly fine. So let me rewrite this here. Y would be the slope times x plus our y-intercept plus 2. So you got a chance to see a couple of problems here where, as a teacher especially, if you're kind of thinking, what are other ways that I can ask some really interesting arc length questions? And we're not looking so much just right now preparing your kids for the AP exam, but maybe even next year, this is a great way to kind of vary those a little bit because they can get a little stale, just asking the same thing. Find this arc length, find this arc length. So I think with that, I'm going to turn it over to Brian and he'll talk you through the rest of the quick checks. All right, perfect. So we're going to take a look at quick check number 4 real quick, and we're going to leave off quick check 5 this morning and jump right into a couple of free response bracket problems. Now we've got our feet underneath us a little bit. So one more quick check. Now we're given a function f of x is given by this natural log of 3x squared plus 2. The length of the curve of f of x from 1 to 4 is given by this definite integral. So again, it's another problem where instead of asking you just to set a problem up, they're going to go ahead and give you an expression and to figure out, can we take that expression and work backwards to figure out the information that we need. Okay, so we're trying to find the value of a. Well, we know that if this is the length of the arc length of f, then we know that this is going to be of the form, the integral of the square root of 1 plus f prime of x quantity squared and then dx. So we can look at our equation here and realize that this little piece right here, this ax squared over 3x squared plus 2 quantity squared, this is going to be equivalent to f prime of x squared, right? And so luckily for us, they actually gave us f in the problem, so we can directly find f prime in this case. So we're doing a little bit of a chain rule problem, a little review of derivative practice. So the natural log's derivative is going to end up being in the denominator, our 3x squared 2, and then times du on top, which would be just 6x. So now we know that f prime is this, and then if we square this, it should be equivalent to our expression that we just came up with, the ax squared over 3x squared plus 2 squared. Well, if we square this, the numerator is going to become 36x squared, and our denominator is going to be 3x squared plus 2 quantity squared. And we can pretty easily check that these two expressions are equivalent, and the only difference is the coefficient in front of x squared and the numerator was a on our worked out problem versus 36 now, so that means that a is going to have to be 36. So if you had an earlier version of this, we printed it off last night, you might have noticed on your document the x was not squared inside of the radical, but we made that little correction. So you're like, wait, the radical's different, that's why. So in this case, a should be 36. Now there is going to be one more quick check, but we're going to list one for you to try. As always, the solutions will be in the Dropbox tonight around 9 o'clock. But you can try this little quick check again. Thankfully, you're only writing an integral expression, but boy, this is going to give you some practice with composite derivatives and keeping your brackets and parentheses clean and organized. Because in the exam, we get a lot of presentation errors, we call them. We can tell the students are doing the right idea, but because of a lack of parentheses or a misuse of parentheses, what they have written on the paper isn't actually equivalent or correct to what we were looking for. So parentheses can cause a lot of easy lost points. So we're going to be careful with use of parentheses and brackets when we get to quick check number 5. So with that said, we're going to do a couple of free response practice problems. Our first one is this that Tony and I are going to do, and I had texted him yesterday. We're going to do this hike, and he was pretty excited about it. I thought he was a little bit too excited. I couldn't figure out why, but I didn't really think much of it until this morning when I realized, he thought we were going on a hike. If you know me at all, you should know better than that. But there's no way I'm going on a hike. So Tony and I are kind of driving around walking on this hike, and we both take different paths. So it says Tony is going to take this path 1 here on the left, and I take other path on the right, path number 2. Tony's path is just 4 line segments, and then this semicircle. And then my path is also 4 line segments, but I have this curve, this f of x graph here, which is going to be e to the x over 2. So part A, who took longer path, right? So I think one of the things you want to be careful for on the AP exam is sometimes students get used to the phrase arc length, and then when they ask questions in context, they don't always make the connection that it's an arc length problem, right? So other ways we can talk about arc length would be who took a longer path, or what is the perimeter of a shape, something like that. All those would require an arc length idea, right? And so when we say who took a longer path, it's really asking for the arc length of these two curves. And so I'm going to start with Tony's path here. So he started the origin. It doesn't matter which direction we go, but basically he's tracing this outline, right? And so the line segment pieces are going to be fairly easy because he goes up vertically, it's going to be a length of 2, then over another length of 2. Man, these problems are always this easy, right? The bottom segment is going to be 5. Now I have 2 little pieces I got to at least think a little bit about. I got to do this half a circle here, and we're not doing area. That's a big issue that students do. We're so used to finding areas under curves. We're not trying to find the area under there. We're trying to find the length of this, right? So the arc length of a circle, remember, is the circumference, and our circumference of a circle is just 2 pi r. Well, we're not doing a whole circle, we're doing a half a circle, and we quickly see the radius is just 1. And so the length of this piece right here is going to be pi times r. It's a half a circle, which is just going to be, in this case, pi. And then this segment isn't so much going to be as simple as the other segments because it's oblique, right? It's kind of diagonally slanted here. So a couple ways you can find the distance of that. You could use your distance formula if you wanted to, or probably a little bit easier method would just be to make a right triangle out of it and use Pythagorean theorem, meaning this is a length of 1, the height of that triangle is 2. So using Pythagorean theorem, we can quickly see that the length of the hypotenuse is going to be the square root of 5. So Tony's total path is going to be 5 plus 2 plus 2 plus pi plus radical 5. And if I were to compute all of that, I believe it's going to be 14.37766, something around that. Now let's go to my path, right? And what's interesting, I think, about these two problems is it looks like one of them is not more than the other one, right? It looks to me kind of like a first that one of them is it's like my path looks like it's more like zoomed in, but these are actually the exact same scale. Okay, so if you were to measure on the paper how far it was from here to here, it's the same as it was from here to here. So it looks deceiving to me because it looks like mine is much longer, doesn't it? Because of how tall it is compared to Tony's. Well, we're going to compute it and actually see whose is longer and how much longer. So the lines here, the line segments are going to be nice and easy to compute to go up 1, and then I have a nice length of 5 here, and then I've got this curve of f of x. So to compute this curve, I got to find the arc length of that, right? I'm trying to find the perimeter of the shape. That's when we have to make the connection that really is asking me for the arc length of this curve. And so if f of x is going to be e to the x over 2, then to our arc length, we have to know f prime, don't we? And f prime in this case, it's a nice chain rule example again. So it's going to be e to the x over, which stays the same, and then by chain rule, we multiply by the derivative of the exponent, or in this case, 1/2. So that means that my length, this part of the curve, is going to be the integral from 0 to 2, those are my x values, of the square root of n plus f prime, which is this whole expression here, squared dx. And this is why I have a little calculator here on the left side, because we're going to use some technology to compute this, right? So I'm going to display my TI-84 screen. Tony always shares his TI Inspire. Tony's an incredible calculator. He's always really cool animations. And I'm sort of primitive. I don't have all the same skills, I guess, but you'll notice where we have really cool calculator demonstrations and models and sliders to show you how things work. It's always Tony doing it because he programs all knows what he's doing. I'm just trying to hit the buttons, right? I'm like the old guy trying to figure all the buttons go. But I went ahead and I put in the function e to the x over 2. That was our f of x function. And then if I go to my main screen, I already pre-typed it in because, like I told you, we would be here for about 10 minutes while I'm trying to all my type functions and
one by one, but this is my arc length formula. So hopefully you can see it here. We have the integral from 0 to 2 of the expression, the square root of 1 plus big here is what we got for our f prime squared, and that ends up being 2.6625 is what we end up getting when we computed that. So I'm going to go back to my screen. I'm going to put you in charge of remember what that number was, just in case I end up forgetting it in the next 3 seconds here, because there's a good chance I could probably do that. So this was 2.6625. I hope I was correct on that, Tony.
Yes.
And then perfect. And then our horizontal length, we can see it's easily going to be 3. And then be careful with the vertical length here, because at first your mind wants to think it's 3, but it's stopping a little bit short, right? And how high is this line? We have to think about where this function f stops, right? So when x is 2 right here, we have to figure out what f of 2 is, and that's going to be e to the first power, or just e, right? So the height of this line is actually e, about 2.7, so not quite going to be 3. And so then the overall area, or overall length for my path is going to be, if I add up all these line segments, 1 plus 5 plus e plus 3 plus that 2.6625. And if we were to add all of that up, it would be a total of, I think it's going to be, help me out here, Tony, give a quick math check on that one. We're ready to add this up real fast. It's funny, I had these written up about a few minutes ago. I believe close, I believe. I'm going to say 14.3808. I think that's right. 14.3808. It's barely more, right, than the other one. It's really, really close. In fact, it's barely even a couple of thousandths, right? I think it's about 3 1,000ths longer. So even though it looks much bigger as a path, it doesn't have quite near the same gap as we might imagine. So it turns out that Brian, I did take a longer path. But now that we look at part B of the problem, what about the greatest area, right? So now we can make another connection to another topic that we might see in this year's exam. So who would have the largest area? Well, Tony's is the kind of shape that we see a lot on FRQs, these little F prime graphs, find the area underneath it. So his will be pretty straightforward. It's going to be just the area of this piece right here, which is obviously going to be 4. Then I have another triangle right here, 1/2 base times height will give me an area of 1. And this little piece here, there's a lot of ways that you could come up with this area, and you can do whatever you want. What I'm going to do in red is I'm going to calculate the area of the square and then cut out this half a circle. So for me, the piece that I want here is going to be the square. Base times height is going to be 4. I'm going to take away from that this half of a circle. So the area of a half a circle is 1/2 pi r squared. In this case, r is still 1. So this little blue area right here is just going to be 4 minus 1/2 pi. So Tony's enclosed area is going to be 4 plus 4 minus 1/2 pi plus 1, which gives us a total of 9 minus 1/2 pi. Now, looking at my path, I have this nice little rectangle here. Let's call it a square, right? Remember, the height is not quite 3. The height of this one was e, right? And the base of this is going to be 3. So this little rectangle area is going to be 3e. And if I got this little piece right here, right, this little area next to it, we're going to have to do the area under the curve of f. So we're going to have to do the integral from 0 to 2 of e to the x over 2 dx. And so we're going to do this one by hand. I didn't put a little calculator by this one, did I? So I'm going to do that in part A to find that arc length. But here, see if we can solve it by hand. We have to do some u sub. It's a very straightforward u sub that maybe you can pop to it in your head. Kind of like a reverse chain rule idea that we integrate x or e to the x over 2. We're going to get e to the x over 2. And then we're going to end up, what is that going to be, Tony? Times 2 in front from 0 to 2. And now we can plug in our limits, and we're going to get 2 e to the first minus 2 e to the 0, which just gives me 2e minus 2. So the area of this little piece right here is going to be 2e minus 2. Now, if I figure out my total area for Brian, this is going to be that 3e plus 2e minus 2, which is going to be 5e minus 2 altogether. And I know that e and pi are not quite known, but it's pretty quick to tell that Tony's area is going to be certainly less than 9, because it's 9 minus half a pi. And then my area is 5 times e minus 2. Well, e is, about 2, it's more than 2.5, right? It's more than, it's about 2.71-ish, right? So this is going to be clearly a lot bigger than Tony's, by a lot larger margin than the initial paths were. So my path also has the biggest area. So if I wrote this problem, I get to win both A and B. So I have the longest path and the biggest area. And the last part of BC1 before we throw it back to Tony and look at another one is let P be the second degree Maclaurin polynomial for f of x. Find such a and use it to approximate f of 2. One of the things that you're going to notice in a lot of these videos is we're going to keep bringing back this idea of Taylor or Maclaurin polynomial, because we want to give you lots and lots of practice and experience of building these in different contexts. So that way this would demystifies them, start to get comfortable with them, and they kind of take away the initial like, wait, what are these things again? You start to get really easy with them, realizing, oh, this is just a way to approximate or clone, right? So if we were going to find P sub 2 of Maclaurin polynomial, or because it's Maclaurin, we know that it's centered at 0, and because it's a second degree, our n is going to be 2. So the framework that how we would build it would be P sub 2 of x equals, and we're taking it for f, right? So the way we build our polynomial is we have to find f of the center, which is 0, plus f prime of the center times x plus f double prime of the center times x squared over 2 factorial. Then our job would be to come up with all of those individual values of f prime, and f double prime, right? So I always like to write the structure out first because it helps me know what I need to solve this problem. So 0, well, we would give it f of x was e to the x over 2, and we know we're going to need to know f prime to do this problem. So f prime is going to be 1/2 e to the x over 2. And we're also going to need to know f double prime, which ends up being 1/4 e to the x over 2. Keep doing our chain rule. And then I got to find out all of those values at 0, right? So f of 0 is just going to be e to the 0 power, which is 1. F prime of 0 is going to be 1/2 e to the 0 power, or 1/2. And f double prime of 0 is going to be 1/4 e to the 0, or simply 1/4. So now we have all those building blocks. We can go ahead and assemble our furniture. I'm going to keep saying assemble our furniture like IKEA. So people start thinking I'm going to keep up with that, not Tony. So I'm officially going to hijack that phrase, Tony, and start making it as my own now. So f of 0 is going to be 1. Then we have 1/2 x, and then f double prime is 1/4. But don't forget we have this divided by 2 as well, so it becomes 1/8 x squared. So that's going to be our Taylor or Maclaurin polynomial. And we're trying to approximate f of 2. All we have to do is plug in 2 to our polynomial, which is going to be 1 plus 1/2 times 2 plus 1/8 times 2 squared. And if you were to work all of that out, all you're going to get is 2.5 or 2.5, which is actually a pretty good approximation, because remember, we're approximating f of 2. In this case, we actually know what f of 2 is because we can plug it in. F of 2 is just e, isn't it? Because f of 2 is going to be e to the first power. And we already said that e is about 2.7. So we're just a couple of tenths off. So this was a couple of examples that sort of started off with arc length, got you into arc length up front. Most likely on this year's exam, you're not going to see a question or an FRQ that just starts off a big arc length problem. It's not a big enough topic in BC to sort of justify an entire free response question all about arc length. And so most likely you might see a problem that starts off one way, and then they kind of sneak in arc length later on in the problem. So I always feel like one of the harder parts of the AP exam is getting used to the idea that students get so comfortable when the problem starts off a certain way, they recognize they know what to do. But yet if a question sneaks an idea in part C or part D and didn't mention it at the beginning, students don't always make the connections of how to like recognize and incorporate those ideas. And so Tony's going to walk us through a really cool problem that does just that, where it might be more similar to how a real FRQ might look, where they're taking you through some other stuff and they sneak in arc length on the back end of the problem.
Exactly. That's what's going to happen when we get to part C of BC number 2. We read the symbol of the problem. It says let g be the function defined by this piecewise front function that you can see right there in front of you. And we know that a is going to be a constant. We are supposed to show in part A that g of x is continuous. So this is a blast from the past. This is going to go all the way back to the beginning of your course, AB curriculum here. And the fact that you're supposed to show this, the word show, probably has a little bit to do with the fact that you're going to have to communicate well. Brian spent a lot of time in the last several videos talking about how important it is for you to communicate. And this is your chance to do just that. Now off to the right, I've written some things down that you wouldn't necessarily have to write down as part of your solution. But this is the concept that we're going to use, this definition of continuity that you learned earlier in your course. So in order for g of x to be continuous at this point where x is 1, 3 things must be true. G of 1 has to be defined, the limit of g of x as x approaches 1 has to exist, and those two answers have to be equal to each other. So it doesn't matter really which order that you tackle these in, you want to make sure that you address each one. So how about we go with the first one, g of 1 is defined. Well, it's not real difficult to show that. Really what you want to do is to make sure that in the domain restriction you have some kind of inequality that's underlying, that's attached to the 1, which just says, yeah, hey, if you want to, you could plug that 1 in for x. Well, let's do that and make sure that we don't have some weird anomaly like a zero denominator or something like that happening. And it turns out that if we were to plug one in for x, we would just essentially have a times the sine of 1 squared minus 1 is 0. And of course, the sine of 0 is 0. And I'm pretty sure that 0 exists, right? It's a number. So we know that we have g of 1 being defined. Okay? Now, the second thing is this idea of the limit existing. And this is where really the bulk of this work is really going to come into play. And we hope as you move deeper into calculus and you start to understand the nuances of piecewise functions, you realize that continuity with piecewise functions is tied so closely to the one-sided limit behavior. And that's exactly what approach we're going to take here. We're going to look at the limit of g of x as x approaches 1 from both sides. Let's do it from the left first. Well, approaching 1 from the left entails looking at the top piece of the function. Those are where all the x values are left of 1. And because we have this fairly well-behaved function that seems fairly continuous, right? The a times the sine of x squared minus 1, we can directly substitute that 1 in, and all of a sudden it's like deja vu all over again. All of a sudden it's like deja vu all over again. You have 0 for that result. We do the same thing with the limit as x approaches 1 from the right. Now this time we get a chance to look at a different part of this piecewise function, the one that's in the denominator. And we have ln of x. Yeah, ln of x I think is pretty continuous. I think we can just directly substitute 1 in, and upon doing so we get 0. I notice these two are the same, right? So our conclusion there is that the limit as x approaches 1 of g of x, well, not only does it exist, it's truly equal to 0. And then if you want to just really put a punctuation point on it, you can see that those two things are indeed equal. Now, I wouldn't think a student would have to write this. In my classroom, if I see a student stopping at 1 and 2, I can see that those two zeros are the same, and I would certainly give the credit for that. But we can certainly make a stronger case by making all three cases. And that is our, we've shown that continuity does exist. This is just a sort of aside. Ryan sometimes talks about how he's not as good with technology. I've seen Ryan do things with GeoGebra that are absolutely brilliant and amazing. And this particular little demonstration I'm showing on the Inspire can be done with a variety of other programs, Desmos being just one of them as well that you have access to. But keep in mind that all of the Texas Instruments software, students and teachers, you have access now to download free versions of those emulators, and you can keep them for up to now, I think, another additional 5 months if you go to the Texas Instruments website. And of course, Desmos is always free and accessible to everyone. But anyhow, if you take a look, this is that piecewise function with that little slider a, and you can see how I can allow a to be a lot of different things. And what I want you to do is just focus on what's happening at 1, and you see that there's always this continuity. Now, I know right there that's a little weird, but there's a slight horizontal segment here going on with that left part of the function. But then when I let a be a positive number again, right, a being a constant, doesn't matter what a is, it seems like I'm always going to retain that continuity at 1, and that's what we showed. All right, take a look at part B now. Part B says, find the value of a that guarantees that the function g of x is differentiable at 1. Well, we have this word differentiable. We can equate that with the idea of taking a derivative. So in order for g to be differentiable, we can investigate g's derivative. So why not? Can you take the derivative of a piecewise function? Of course you can. It's not a very difficult thing to do. You just have multiple derivatives to take. So in taking the derivative of the top piece, what we have to do here is think about the chain rule that's going to be used. So this a constant is just going to sort of plop straight down. The derivative of the sine of something is just the cosine of that same something. But then we need to multiply it by the derivative of that something, and that's why I left that little bit of room out front to put that 2x. And then my restriction would be 0 less than or equal to x, less than or equal to 1. I know in certain cases I would have my students maybe not underline that 1 because maybe we don't know if we're differentiable there or not. But this problem is saying that yes, we are differentiable at 1. Let's find that a that's going to make that happen. So we continue that, and we take the derivative of what's on bottom, 1 over x, and we have x greater than 1 here at that point, right? All right, so what is this a going to be? Well, in order for this differentiability thing to be happening, we have to know that the limit of our g prime as x approaches 1 from both sides agree. We don't want to have slopes coming in at each other that are too abrupt of a change from one to the next. So we want to make sure that that limit is nice and well behaved. So we take the limit as x approaches -1 of our friend g prime, which is just a matter of inserting this 1 into that expression up here. And then, ooh, interesting. What about this a? I'm going to erase that x because I'm going to need to replace it with 1. Well, what about that a? Well, the whole point of this problem is to find that guy. And that a is going to be really important for us when we look at a future part of this problem. So let's go ahead and replace that x with 1. Here's that a, and we're going to replace our 1 with 0. And I think that we can figure that out. I think that's 2 times a because the cosine of 0 is 1. And if we take the limit as x approaches 1 from the right of our g prime, of course, 1 over 1, nice and continuous, at least at x equal 1, and then we have the value. And then we put the two ideas together, right? 2a has to be equivalent to 1, so that forces a to be equal to 1/2. Okay. Now I have an idea here, and sometimes the best teaching things are ones that are done really on the fly. And I promise you, I have not rehearsed this, but I'm interested to see what would this graph look like when a is a half. Now the problem with that, I think I have to change the settings of my slider and make my step size allow for half increments. Oh, I hope this works. If not, well, we can't edit this. It's live. Well, let's see what happens. So let's take this back to where a is a half. Now right now, when a is not a half, I don't know if you see, but there's a little bit of a sharp turn here. It's pretty subtle, but it's sharp enough to be construed as not differentiable. And if I keep going back, by the time I get a to be 0.5 or 1/2, that's going to be a little bit more smooth. We just don't have that sort of rough, sharp turn or cusp sometimes, as we call it. And we could probably see that a little bit better if I zoomed in. Okay? So let's go ahead and finish up our part C with finally an arc length integration to this problem. And that's what Ryan was talking about. We now finish with arc length. Right, but do not evaluate an expression involving one or more intervals that gives the arc length from 0 to 3. So what we're going to do here is we understand that we need the derivative of g, and that's important. And what I'm going to do is take that derivative and just basically recopy it very quickly from our previous slide. But the issue now, remember that a that we talked about? Remember the a being 1/2? That has to be a thing. We have to use a to be a half. And the reason for that is because we need this continuity issue for this derivative before the arc length formula can apply. And I think that's one of the key elements of this particular problem. Very well written by Ryan. So we have this expression for our derivative, and at that point we can just go ahead and realize that for this arc length, we have to divide it up into 2 pieces. So we'll integrate from 0 to 1 of our traditional 1 plus, and I'll take this expression and square it. I'm not going to do a whole lot to it, except for maybe cancel the 2's, but that would take care of that expression squared. And then to that, we shall add the integration from 1 to 3 of the square root of 1 plus, and then our g prime there is 1 over x quantity squared. And that takes care of your arc length of that particular piecewise function. And with that, Ryan, I'm going to turn it back over to you to let us finish up.
Awesome. So we're going to look at just a couple more quick examples. We're not going to do all of these because we don't have time this morning, but I want to share at least a couple of pieces of a couple of questions as we finish up to show you how these things kind of tie together with a lot of interesting other ideas. So I hope one of the things that you've noticed about these lessons is we always try to tie in a new idea in the midst of other ideas, right? Because the exam is so good at making sure that you can weave ideas back and forth, kind of jump back and forth between different topics that you've learned this year, all in the middle of one single problem. And so we always try to do that to keep you on your toes, but also to prepare you for what you might see on this year's exam. So differential equations is always a topic. And consider the continuous and differentiable function f, so that the arc length of the curve of f from 0 to 2 is equal to the area bounded between the graphs f and the x-axis from 0 to 2. Show that function f, which we don't actually know what it is, right? Satisfies the differential equation y prime, or y squared, sorry, minus y prime squared minus 1 equals 0. Holy cow, that's a lot of stuff going on there, right? So let's think how we might write this down. This would be what we would call a very verbal step, right? Every AP exam has different steps, meaning how do they give you information in the problem? Sometimes they give you a graph or a table or an equation. This would be a nice verbal problem because in the original structure of the problem, there's no equations, there's no pictures, there's no tables. You have to read the words and you have to come up with your own equation, right? And so it says here that we can graph f. Let's just pretend we have some graph f that tells us it's continuous, differentiable, and positive. So let's just say it looks something like this, right? It's continuous, differentiable, and positive. It's telling me that the arc length of f, right, from 0 to 2, the length of this is equal to the area under the curve. So how are we going to deal with that? Well, what if we just set up a problem? So the arc length, well, we can find arc length, couldn't we? The arc length formula is the integral from 0 to 2 of the square root of 1 plus f of x squared, right? That's our arc length formula. And it says that is equal to the area under the graph of f. Well, how do I find the area under the graph? Well, we would also integrate rate from 0 to f of x dx. So those two intervals are equivalent. Notice they have the same bounds, don't they? So they have the same bounds and they're equal to each other. And that means that their expressions during that interval are also going to be set equal to each other. So we can now set f of x equal to the square root of 1 plus f prime of x squared dx. Now, I will point out one little small word I slid into the problem to make this work. I said that f is a positive function, meaning we know that, what if f went up and down and negative and all this kind of other stuff, it didn't quite work. Well, these are going to end up being equivalent in this case. So we can set them equal to each other, and then we can use this to say that means that y is going to be equal to f of x, right? And then that's also going to be equal to that value right there. So going back to our differential equation, if this is what f of x equals, which is y, and that equals this, we can now verify our differential equation. And so in this case, y squared would just be f of x squared, or since they're equivalent, that squared, right? And so we can take this quantity squared and then minus y prime squared, right? Well, remember, if y is f of x, we already know that, and that means that y prime is just going to be f prime of x. So that means that we're going to have minus, in this case, f prime of x squared minus 1, and we're hoping, for a question mark here, that this equals 0. Well, if I square this radical, we're going to get 1 plus f prime of x squared minus, and here we're going to have f prime of x squared again minus 1. Well, look what's going to happen. These f prime of x are going to cancel, because we're subtracting them, and the 1s are going to cancel, and what do we get? We get 0 equals 0, which worked. The function f that we're talking about did in fact satisfy that differential equation. Now, part B, we're not going to do a neat little question to see if we can make the connections that we just made, right? And so I give you an example of a function, g of x, which actually satisfies that requirement. You might be asking, okay, is there really a function whose length, whose distance is equal to its perimeter? Well, yes, there are several functions, but one of my g of x function right here is 1/2 e to the x plus 1/2 e to the negative x. Is to find the arc length of that from 0 to 2. And my challenge to you, could you do that with no calculators? And the trick is making a connection from what we had earlier. So if we meant about our initial information, we can solve this problem kind of in an easier way than actually finding the arc length. We can find the answer a different way. I'm going to lay that challenge out for you to see how you can do with it. Hopefully it works well. And then we're not going to talk about BC5 today, but I love this question. It connects so many rich ideas together. We're given a table of f prime, right? We have an f prime function, and then we're told some information, but really it's an arc length stem in a really different way. So it says the arc length of f, and I kind of drew, this is not a picture of f, by the way. This is a picture of s, but we'll come back to that in a minute. But the arc length of a function f is represented by this integral, right? This is the arc length formula. So s will represent the actual arc length. So the arc length is going to be the interval from 0 to x of this expression, right, which looks pretty familiar, I hope. So that's a different way of thinking about arc length. So what we're going to do is we're going to be approximating s, the arc length, in a couple of different ways. We want to see, hey, can you do a left Riemann sum to approximate s? And then after we do that, we're going to say, okay, could you use to approximate s of 8? And then once we get through the Euler's method, then we're going to say, okay, now can we use a second degree Maclaurin polynomial to approximate s of 8? So we're going to approximate s of 8, which is the arc length from 0 to 8, 3 different ways, and see which ones are close, which ones maybe aren't close. It's a little bit trickier than you might realize, because this table gives you f prime, which is definitely useful, right? But we're approximating f, we're approximating s. You got to figure out how that f prime can relate to what we need for those three problems. So definitely one to be a little challenge for you to see if you can really connect not just arc length, but arc length with Riemann sums, with Maclaurin polynomials, with method all in one problem. All right, so with that said, our favorite time of the day, tweets with Tony. Tony, what do you have for us this morning?
We have got for our AP Teachers Rock this morning, Mr. Huckabee, my AP Calculus teacher for 2 years now. Such a wonderful teacher and a caring individual. He always made our lessons and days in his calc room fun and worthwhile. So congratulations, Mr. Huckabee. Your students are definitely fortunate to have you. And as far as our AP Students Rock, we're going to give a little shout out to the West Coast here. Super proud of it. Deeply miss my AP Calc BC students. After 3 years together, I got all the feels as we prepare for our AP Calc exam on May 12th. So great job. Congratulations. That's from East Bay Innovation Academy out in Oakland, California. Big shout out to you guys. Great school, great teachers, great students. And Brian and I have a very, I guess, a soft spot. We love the teachers out in California. We've been so fortunate to go out and work with them on many different occasions. So great job there on the West Coast. As always, students, if you or your friends are having trouble with internet access with different various forms of hardware, please have them reach out to cb.org/tech, and they'll certainly get that taken care of you. I'm excited. Next week, Brian and I have our Connecting AB to BC review phase of this particular YouTube live, and I'm really excited. And I'll tell you what, it's the highlight of my day. My friend, working with you is absolutely a joy, and I look forward to it every morning. You're a genius, and these problems are fantastic, and they just seem to keep getting better and better.
Well, I think Tony's just trying to butter me up for that own $20, and he's hoping I'll pay him back if he keeps saying nice things about me. But Tony, you are always a great friend. Tune in about Monday. I hope you guys will join us as we start wrapping more and more AB topics in with our BC topics. So without further ado, our good friend Anthony G will take us. Thanks, guys.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus. Taking polynomials. Infinite series. Differential equation. Calculus. Taking polynomials. Infinite series.
Good morning, and welcome to everyone joining us for today's episode of AP Calculus BC Live. Thanks to viewers like you, this is now the #1 rated BC Calculus review show on YouTube Live at the 9 a.m. time slot, hosted by two Indiana teachers named Brian and Tony. So we certainly thank you for your support. Not only do we have a great show for you today, we have a really awesome week ahead as we start our Connecting AB to BC series of lessons. So we'll talk about that, what that entails as we move through the video. So, but basically, you're going to see, obviously, limits and continuity as the core structure of our lessons today. Those are AB topics. And then these free response questions that we talk about will sort of segue into these larger topics in AB and BC that might be partially scaffolded by those limits and continuity topics. So we're really excited about that. As always, you have the ability to download any of the materials that you will want to use for any of our lessons in the description below the video. And you can certainly do that. You have time to take care of that now, print that out, and you can certainly follow along with us. And we would really appreciate that. And I know your teachers would as well. Once again, my name is Tony Recker, teacher from Avon High School in Avon, Indiana. And I'm joined by my wonderful, awesome friend, Mr. Brian Passwater, a teacher at Speedway High School. So Brian, you last night showed me a very cool math trick. Any chance that you could share that with us today? Put you on the spot.
Ooh, yeah, I think we might have some time for that. Maybe we'll use that as a teaser today. So maybe about halfway through our lesson, we'll take a quick brain break, and I will show you the same math trick I showed Tony last night, which was, I think according to you, it was a quote, life-changing. Yeah, it said raise your coolness factor by level of 12. That's pretty high for one math trick. So if you want to see a really fun, cool math trick that will amaze all of your friends and family, and raise your coolness factor, stick around. In about a half an hour or so, I will show you this. I lost my camera there, Tony. In a half an hour, I will show it to you. Sounds good. Sounds great. Sounds great. Awesome. So before we get to that, how about we jump into some problems today, and then at the end of the lesson, Tony will wrap us up and show us what we're doing next week, and kind of where we're going from here. So we are going to be looking today, like Tony mentioned, at limits and continuity. And of course, my screen wanted to share the wrong thing. So this is, I think, Tony, this might be our first major technical issue on the screen. It had to be, of course, me that did it, because like I mentioned last week, you are much more tech savvy than I am. And so for me, if there's one of us that was going to mess this up, you knew it was going to be me. So there we go. How about that? Hopefully we're sharing the right screen now instead of that screenshot that I had earlier. Tony mentioned we are doing limits and continuity. And so we're going to go through a couple of quick checks before we jump into these response problems that Tony mentioned. And the first one is a little activity that I made. Maybe you've seen it before. This is all new problems, but it comes from an activity I shared with some calculus teachers a while back called odd limit out. And how it works is you have different problems, and each problem has 3 statements. statements, and then you would find the answers to all 3 statements. And if you did it correctly, 2 of the statements will have the same answer, and then one of them will be a different answer, and that's the odd one out. That's what your answer is going to be. So if you do these problems and you get 3 different answers for the 3 statements, you know you made a mistake, and all 3 answers are the same, you obviously made a mistake. But hopefully you'll get 2 of the answers are the same and 1 answer that's different. And so we're going to actually start on problem number 2 here. I'm going to skip problem number 1, and we're going to jump into problem number 2. So you're going to be able to go back and do problem number 1 if you'd like to do a little bit more practice once we're done with this. So statement number 1 says, find the limit as x approaches 2 from the right of h of x. Where a little plus sign means from the right, and we're given a graph of h. And so the limit as x approaches 2. Remember, a limit just means, what if you were on the graph of h and you're approaching an x value of 2? And the plus sign means we're on the right side of 2. So we're somewhere over here. I put a little blue dot there on the screen, and we're going toward the value of x approaches 2. And we'll notice, wait a minute, there's a hole in the graph there, and there's some kind of weird jump, right? The other part of the graph jumps up here. A lot of weird things are happening there. This is the whole reason why limits are so valuable, because we're not able to plug 2 into the function because it would be undefined, but yet we can evaluate limits, especially for different directions. So h approaches, or x approaches 2 from the right just means we're on the graph of h. We're getting closer and closer and closer to the point where x is 2. And a limit, remember, means where are you headed? So don't be fooled if there's a jump on that side or there's a hole or a random point somewhere else. A limit is simply asking if you're on the graph and you're going toward that x value, where do you think you're going? Where does it appear you're headed? Well, we're clearly headed toward this hole in the graph, right? And so a limit doesn't need a point to have an answer. It just needs to have a clear direction where you're going. So in this case, we're heading toward that hole, and the y value of that hole in the graph would be at 0. So that's our limit on the right hand side. And then the second statement is the limit as x approaches 2. Again, if you can't see it, there's a little minus sign there, meaning from the left hand side. So we're still on the graph of h, we're still approaching 2, but now we're going to start from the left hand side of 2. I'll just put in red, and we're still approaching 2, but from the left hand side. Well, in this case, starting on the left, we're now approaching this hole in the graph, and that hole in the graph has a y coordinate of 2. So notice neither one of those have a point on the graph, but we're not concerned about that. We're just concerned about where we think we're heading from the left and from the right. And then the third statement is going to be, what's the limit as x approaches -2? We don't see a left or a right, we just see the -2, which means in order for this limit to exist, we have to have the same answer from the left side as we do from the right side. And so if we're approaching -2, the x value from the left and from the right, those 2 segments in green are in fact approaching the same value, and they're both approaching this point right here, which happens to also be at 0. And so for problem number 2, I've got answers of 0, 2, and 0. The good news is 2 of them did match, right? We got 0 for 2 of them, and then 1 of them was different, and that's going to be our odd limit out. So for problem number 2, the odd limit out is just going to be that answer of 2, because that was the one that was different than the other 2. Let's try one more here. Problem number 3. Now we're going to take the limit as x approaches 3. And just like before, there is no left and right side to this problem, it just says 3. So we have to make sure that as we approach 3, we're coming from both directions. And now we have something a little bit different, right? We still have the same hole, which doesn't really make us too nervous, but we have this random point kind of placed above here, right? So this is where it's important to know the difference between limits and then function values, and then tying those together later will be the idea of continuity. But if we're approaching x equals 3 from the left and from the right, remember we said it only depends on where you think or where it appears that you're heading. And so if I'm following along this path from both directions, both of these directions are going toward this location, right? This is where they're heading. And so since they're both heading toward that same location, this little hole is going to be our limit. That's where we appear to be headed. In this case, that's going to be a value of 1. So we're able to ignore that point because the limit is just where the graph appears to be heading, not where the actual point is if there is one. And then the second one, h approaches 6 of h of x, again from both directions. So coming from the left hand side, as we approach 6, we're going this direction. This little dotted line indicates this is a vertical asymptote. And then coming from the other side of 6, we're approaching this way. So this really brings up 2 interesting points. Number 1, these are unbounded, right? They're going up to infinity or down to negative infinity. If a limit is unbounded, it's going to infinity. Sometimes you can write infinity down, but that's also an example of a limit that does not exist. In this case, though, these 2 limits are actually approaching different infinities. They're not even approaching the same infinities. They're going different directions, right? If your limit from the left and limit from the right are approaching different directions or different values, that's one example of why a limit does not exist. And so we would say the limit as x approaches 6 does not exist. And then looking at the third one, x approaches -1. Again, we have to approach it from both directions. So it doesn't tell us just a one-sided. And so as we approach -1 here from the left, we're going to be approaching along this path. And if we approach -1 from the right, we're approaching along this path. And notice from the left-hand side, we're approaching 2, but from the right-hand side, we're approaching -1. And so now, again, another example where from different directions, we're approaching different values. In order for a limit to exist, we need that left-handed limit and that right-handed limit to approach the same answer. This is another example of a limit that does not exist. So for problem 3, we have 2 answers that did not exist, and then one of them had a value of 1. So our answer there is going to be simply 1 is the odd limit out. So that's a couple of graphical examples of how we approach limits. And now we're going to connect this idea of limits and points to continuity. And so continuity is a step higher. So in order for a function to be continuous at a given x value, we have to have 3 conditions met. Number 1, the limit as x approaches c from the left has to equal the limit as x approaches c from the right. This is a fancy way of just saying the limit as x approaches c of f of x exists, right? That there is a limit. It's kind of equivalent idea of saying that. And some of your textbooks will just say that. What I found with my students, when I used to tell them the first step to show the limit exists, when they're given a piecewise function, they don't necessarily remember or think, oh, I have to check the left and right limit for a limit to exist. And so I think Tony and I are pretty similar in the fact that we automatically tell our kids to check the limit from the left equals the limit from the right, because that's synonymous with saying the limit exists, and it tells you, oh, I got to do 2 things here. But not only can the limit exist, not only do we have to approach the same value, we have to make sure there's actually a point on a graph, right? There can't just be a random hole there. There has to be a point on the graph, so the function has to exist. And then finally, not only do we have to have a limit, and not only do we have to have a point, we have to also make sure that the limit and the point have the same value. So we don't have a hole on the graph with a random point somewhere else. So all 3 of these things have to happen in order for us to show that a function is continuous. If any of these 3 things fail, then the function is not going to be continuous at that point. So we're going to look at a couple of examples of this. And on the bottom here, we have the reference to kind of remind you. And these are going to be really important for response questions. Here's kind of like your AP exam tip number 1 of the day. When we're doing for response questions, a big part of the exam is how you communicate, how you use theorems and definitions, and how you use notation. All those little things that students kind of overlook sometimes. We're so used to, at least my kids are, thinking the answer is what's most important. How do I get to the final answer, right? I might do some work on the side for my own benefit as a student, kind of scratch work, but here's my answer, here's what you should look. Whereas the AP exam really is you telling a story, right? Each problem is you telling a story, and so you're trying to communicate to us what you were thinking every step of the way. And so it's really the burden is on you as a student to communicate. We don't get to guess what's inside your head, what you knew and didn't know. If you don't put it down, we can't give you credit for it. So make sure that you show the proper steps. And then number 2, show that notation. A lot of times students will look at the 3 steps and kind of know what it wants you to do, but then you won't use the proper notation, and that's going to end up costing you at least full credit. So maybe you won't get all the points on a problem that otherwise you really did understand and know how to do it. So continuity is a really good example of that, where we see a lot of students that clearly from their work understand what continuity is, but yet their notation and their communication was either lacking or missing, which results in them not getting full points. And so it's always sad when we see that, but hopefully from today you will be reminded, or you'll reinforce exactly what you need to show on the exam, so that way you get all of those points that you deserve. And so here we're going to try a quick definition of continuity question. So part A, we have 3 functions f, g, and h. Is f continuous at x equals 2? And give a reason for your answer. Well, if we're going to check for continuity, when a question asks us for continuity, that's when we know we're going to check these 3 steps. And so I always like to label them. Step number 1, we have to show the limit from the left equals the limit from the right. So we're just going to work that out. We're going to say the limit as x approaches 2 from the left of f of x, and then we're going to show the limit as x approaches 2 from the right of f of x, and we're going to hope that they end up giving us the same value. And so the limit as x approaches 2 from the left, we're going to use this top equation here, because this is for values that are less than or equal to 2, or the left-hand side of 2. And so when we're doing this, just good communication to not just put your answer, but to give some kind of evidence that you knew which equation to plug it into. And so we're going to go ahead and show that the limit from the left is going to be 3 times 2 minus 5, which is 1. So notice I didn't just put down 1, I showed this kind of intermediate step of me plugging 2 into that top equation. And the limit as x approaches 2 from the right is going to be cosine of 2 pi if we plug in 2 for x here. And then cosine of 2 pi on the unit circle is also going to be 1. So notice our first requirement is met. The limit from the left did in fact equal the limit from the right. And then we're going to go to the second requirement, which is does the point exist, right? Just because the graph has the same limit, it means they're heading toward the same place, but can we guarantee there's a point on the graph? Well, to do that, we would have to check f of 2 in this case, and can we plug in 2 into either of those problems? Well, this equal sign here on the top tells me, yeah, we can plug in 2 into the top equation, right? Because it has the equal sign, so f of 2 is just going to be plugging in 2 to the top, which happens to be 1. We already found that. And so now the third step is to show that those values are the same. Well, we can clearly see we had the same answers for each of those. And so now for our third step, we can just verify, hey, guess what? The limit as x approaches 2 from the left of f equals the limit as x approaches 2 from the right of f, which happen to equal f of 2, right? Notice how I plugged in 2, and then I think one of the big things that Tony and I see is that it's really tragic is students will do part 1 and part 2 beautifully, and they'll get to part 3, and they'll have the right idea, and you know what we see a lot of students doing? They forget to put the f of f there, right? You're never allowed in math to write a limit with a number there equals something, right? There has to be something next to the limit, an argument, right? There has to be an argument there. Putting a limit equals something is equivalent to kind of saying square root equals. Like, you have to have something inside of the square root. You have to have an argument, something you're taking the square root of. Same thing with limits. So never in your life should you see lim equals lim without the function being named. That would be all the beautiful work and then one bad notational error, which means it's going to probably prevent you from getting the full credit on that question. So we were able to check all 3 of those pieces. They were all true. So since they were all true, we can reach our conclusion and we can say, yes, f of x is continuous at x equals 2. And I have all my work clearly laid out like this. That's all we have to say. This is our reasoning, is our work. This is our justification by saying all those things. So let's look at one more. I'm going to skip part B and go straight to part C of this. It's looking at it a little bit differently, which is we're now looking at the function g, and we're going to ask not is g continuous, but find the value of k that makes it continuous. So we're still using our idea of continuity, and the real idea here is if g is going to be continuous at 3, that means the limit as x approaches 3 from the left is going to have to equal the limit as x approaches 3 from the right. That's the only way for a function to be continuous, is that first step has to be true. Well, if I take the limit as x approaches 3 from the left, I'm getting this top piece here. I'm plugging 3 in for x, right? Not for k, but just for x. So from the left, we're going to get 9k minus 6. I plug in 3 for x's, and that should equal the limit as x approaches 3 from the right. And I'm going to plug in 3 to the bottom, which is going to be 6 plus 3k. Now we have a nice little equation for k. We can solve this pretty easily by putting the k's on the same side and making it equal 12, and then we're going to get k equals 2. Now we can quickly verify the other answers are going to be true, that we do have a point because we can plug in 3 to the bottom. And if we check all of these left, right limits and the function value, they would in fact be the same. We don't have to check all 3 of these because the question wasn't to see if it's continuous. Just want to find this value of k, which means I know the left and right limit are going to have to be the same. So that's quick check number 2. And then quick check number 3, we're just going to look at one really quick problem just so you can see a combination. We started off with a graph, then we went to a piecewise function, and now we're going to mix it up a little bit. We have a graph and a piecewise function. And so quick check 3, part B says, is the function k, now notice k is the middle one, right? I'm on B if you're following along. We skipped A. Is k continuous at 2? Well, our first requirement, remember, if you're from that previous slide, is that the limit as x approaches 2 from the left needs to equal the limit as x approaches 2 from the right. And so if we go ahead and find these 2 values, the limit as x approaches 2 from the left is going to use this top function. So we're approaching 2 from the left of the graph of m. Well, here's the graph of m. I have to approach 2, but from the left-hand side. So here's when x is 2, but coming from the left, we can see we're following this path, and we're going to be approaching this hole in the graph, which is at 2. And then if we're going to approach 2 from the right-hand side, we're now following the graph of p of x from the right-hand side. So here's the graph of p. We're still going to be approaching 2, but now we're coming from the right-hand side, and we're going to be approaching this value right here, which is simply 1. And right off the bat, we can see the limit from the left does not equal the limit from the right. And so we can stop. If all 3 conditions are met, we're done. And so is k continuous at 2? No. K of x is not continuous at x equals 2. And then all we have to do is kind of mention which one of those 3 rules were broken. Well, which one was broken? The limit from the left, x approaches 2 from the left of k of x, did not equal the limit as x approaches 2 from the right of k of x. So notice all of the notation and work that we showed on proving that things are continuous. Continuity is a really good problem, but I could definitely see the exam putting on this year's test with this new free response style. It tests a lot of things, but also it shows you the need to communicate clearly. So that's going to be our quick checks. There is a quick check 4 in the notes or the materials. We're not going to look at quick check 4. These are advanced limits, and I will tell you on a normal year, you might see one of these problems on a multiple choice question. The odds of the chances of being on free response is virtually 0. They're very, very challenging. And so if you want to try quick check 4 on your own, there's lots of really tough ones on there. And you see the answer key, you're maybe thinking you got all those wrong. Possibly. Don't panic. If you came to quick check number 4, it's probably not going to be tested this year. So that's why we're going to skip it for right now. It's there for teachers that can use it next year. But don't worry too much about quick check number 4. So now Tony's going to transition us now to going from these quick checks to these response problems that are going to be connecting A, B to B, C. So Tony, what do you got for us?
Certainly, we're going to dive in here to BC1, and it reads the graph of the twice differentiable function f is to the right in the figure, or above in your particular handout, for the interval -3 to 6. The area is bounded by the graph of f of x, and the x-axis are labeled in the figure. It is also known that f has relative extremes, at x equal -1 and x equal 2. The function g is not explicitly known, but g prime, the derivative of g, is defined by the piecewise function that you see there. G prime is f of x from -3 to 0, and g prime is x times f prime of x from 0 to 6. So certainly a lot's going on in terms of the stem and what information is being provided. But the question is a familiar friend: is g prime continuous at x equals 0? Give a reason for your answer. So we're going to go ahead and organize this in a very similar fashion. Now we don't have our little reference there in the corner, so if you have to flip back to the definition of continuity point, that's certainly okay. If you think that you can kind of memorize it and put it together as we move along, that's all even better. So the function g prime is what our focus is. So we're going to go ahead and attack it from the one-sided limit standpoint. That's the way that we always want to deal with piecewise functions with continuity. So we think about, well, what is this limit of g prime as x approaches 0 from the left? Well, g prime can be 2 different things, right? 2 different definitions. But as we are on the left side of 0, right, that means that we're going to be looking at the top piece. So basically, taking the limit of g prime is every bit the same as taking the limit of f. Well, what can we do about that? Well, you'll notice that the stem of the problem mentions something about twice differentiability here for this function of f, which implies that f and his derivatives are going to be continuous. So that does give us the ability to sort of evaluate this function specifically at that 0, something I refer to as a green light in my classroom. So we can actually fill in that x with 0 because of that continuity of just the f of x by itself. And then we look at this f of 0 and we think about, well, what are we going to do about that? And we see the function f up here very nicely displayed, and we see that the y value there is certainly equal to 0 when x is approaching 0. So that takes care of the left-sided limit. Let's do the same thing for the right side, shall we? So we have the limit as x approaches 0 from the right of our g prime. This time g prime takes on a little bit of a different look. As we are moving towards 0 from the right, that's the same as being larger than 0. We find that we want to use the definition denoted by x times f prime. So we'll slip that in place of the g prime. And again, we have a situation where individually these 2 pieces are continuous. So we would be allowed to invoke some limit properties. We can bust them apart, use 2 separate limits so that the limit of product is the product of the 2 limits. Or we could just really quickly see that on the fly, and we could directly substitute 0 in for x, which works fine. We could go ahead and substitute the 0 in for x again in the f prime. We have something like this, which temporarily might cause us to be a little anxious because we have to think about what's f prime of 0. That's a good question. If you go to this graph and you think about, well, what is the derivative of that graph at 0, it might be a pretty tough thing to do, but it really doesn't matter, does it? Because we have this 0 alongside that's going to multiply and cause the result to be 0. So we can see that the 2 one-sided limits are the same, which does say that the limit of g prime as x approaches 0 from both sides does exist. We'll move on to step 2. Step 2, I think in our chart mentioned finding out or discovering whether or not g prime was defined at that particular value of x. So we think about, well, what's g prime of 0? And by virtue of this inequality symbol being underlined, that means that we are allowed to plug 0 into the function as long as it does provide something that makes a little bit of sense. And it turns out, kind of like what we did before, 0 times f prime of 0 comes to the forefront again. limit, which gives us a 0. We see that everything here on the right side of the equal signs are all in alignment, so that means that the limit as x approaches 0 of our function g prime of x was indeed equivalent to the right side, which is also equivalent to the value of the function there. So all three ingredients of the definition of continuity of a point are satisfied, so we can finally say, well, therefore, yes, g prime of x, make sure you reference the right function, g prime of x is continuous. You can certainly abbreviate the word continuous at the point at x equals 0. So that takes care of our part A. I'm going to gloss over part B here. Part B, it reads somewhat similarly. It asks to show that g prime of x is differentiable, and that would involve you investigating, first of all, the derivative of g prime, and then doing that same sort of attack with those one-sided limits and using the definition of continuity there as well. Now, the reason why A and B are structured in this problem at the very beginning is because we're going to use those in a later problem that you're going to see in a moment. I want to also skip part C. I'm going to invite you to definitely take a look at this, sign up for homework. We'll have the key available here with a few hours, maybe this evening or tomorrow morning, and you can easily find and classify any local extrema for g of x on that interval -3 and 6, so it invokes another really powerful AB idea. But I would like to talk a little bit more in detail here about part D. We haven't talked about these special existence theorems a whole lot. They kind of showed up here and then in some of the free response questions. But part D says the conditions for the mean value theorem are met for g prime of x over the interval -3 to 5. That's probably has a lot to do with part A and part B being the way that they are. Apply the mean value theorem over the interval -3 to 5, and in doing so, that will guarantee a value of c such that g double prime of c is -17/8. Our job is to use that information to figure out what the value of f prime of 5 is. So again, it's nice that we don't have to state the conditions of the mean value theorem. Right? It says that they've already been met, so you don't have to say that we have this function g prime that's continuous, we have this function g prime that's differentiable. Those are already established. So what we will do is think about, well, what does this mean value theorem say? Well, it says that we've got this second derivative of g, this instantaneous rate of change, if you will, right? And we know that that's equivalent to -17/8. But by definition of the mean value theorem, that says that we would just simply take the average rate of change of the original function that was given. Now, that original function is once again g prime. So you're sort of working on a different level of a derivative here. Normally, when you apply the mean value theorem, it might be for a function f, and then you would take the average rate of change of f by subtracting a couple of f primes over some x's. Now this original function is g prime, and we're going to use g prime at 5 minus g prime at -3 as our numerator, and we'll divide that by 5 minus -3. And of course, that's going to be equivalent to the derivative of g prime, which is g double prime. So all we need to do is correctly evaluate each of these particular function values. So g prime of 5, well, once again, 5 is going to take us to the second part, right? The interval from 0 to 6 is where 5 lives, and so we'll use x f prime, and we'll plug our 5 in there as such, and then we'll drop in our minus sign, and then g prime of -3, that is going to have us move up here now, where x is defined to be -3, and then that produces f of -3. All right, and then of course our denominator is going to be 5 minus -3. Let's simplify a little bit. 5 times f prime of 5. Well, f prime of 5, that bothers me a little bit. We really don't have the means by which to find f prime of 5. I mean, we're talking about this point right here and whatever his slope of the tangent line is, but we really don't have any way of figuring it out. And besides, isn't that what the question is asking anyway? So let's move over to the f of -3. So we can't do much with this, but we can find f of -3, and we just go to our graph, and you can see right up here that the y value f at -3 for that function f, right, is going to be +2. All right, and we still have the denominator of 8. Now at this point, we just basically have to sort of equate this all the way back to the -17/8. And to save a little time here, we can see that the two denominators are both 8, right? So we can go ahead and cancel those just by multiplying both sides by an 8, let's say. And it's pretty academic from this point out. Just make sure that you get that negative sign in with that -17. So if we add 2, we're looking at -15, and then once we divide by 5, we have our -3, and that's the value of f of prime of 5 that we were looking for. Let's move on to part E. We told you that we're going to try to invoke some BC ideas, right? And here's our chance to do that with BC1. So we were asked here to evaluate the definite interval from 0 to 6 of g prime of x. Okay, seems pretty simple enough. Noting that the boundaries of integration span from 0 to 6 pretty much shines the spotlight on the bottom piece of that function. Remember, all these problems seem to revolve around this piecewise function g prime. So what I would suggest is that we go ahead and get a little clearer look of what we're actually trying to integrate. G prime is nothing more than x times f prime of x. Okay, now we take a step back and we start to think about all of the various integration techniques that we have at our disposal. Our hope is that you see that this seems tailor-made to use an integration by parts. In fact, we've seen some problems kind of like this before that have that vibe to it. Again, your AP exam this year is not going to consist of integration problems that are going to be written in a very analytic way, right? You're going to see them disguised with function notation and things of that nature, and that's what you want to make sure that you're really on top of and that you can recognize. So in this particular case, I'm going to let u be my x. And I know I always set mine up just a little differently. I like to write my dv sort of on another line, a line below, only so that students can kind of understand the difference between differentiation and integrating. Differentiation is going down, right? Begins with the letter d, so we take the derivative of u and we get 1, or we can swing the dx over. And integration, boy, I wish integration started with u, that'd be cool, right? But it's close enough, it's a vowel. So if we integrate dv, we get v, and that of course we just do away with the prime notation, and we have just f of x. And then we just remember that our formula is u times v, starting with that first. So we go u times v, which is x times f of x. And of course, that's outside of the integral, so we can start evaluating our boundaries. And then we would subtract v du, which would be these two components, and that would also be housed in that original integration. So yeah, something like that. There's a variety of ways to structure integration by parts. If you're doing something that's been very successful with you, then there's probably no reason that you need to change. And of course, you could use a tabular method for this problem as well. So if we continue with this, we plug in our 6, and we get 6 times f of 6, and we'll subtract, and we plug in our 0, which is 0 times f of 0. So we have that pretty much taken care of, and then we'll subtract, and then we see this integration of f of x that is very conceptual in nature, nothing really to integrate analytically, but we do remember that our different f of x was this graph up yonder, right? There's a Hoosier word for you, yonder, and integrating from 0 to 6 is just going to ask us to find the area between the curve and the x-axis. And we notice that we have a bit of area here that's going to span the region from 0 to 4, which I just covered up, which is going to be 7, and then we have this area from 4 to 6 that finishes that particular interval of 3.5. However, signed area is going to be taken into consideration because this area is below the x-axis. So we're going to take the positive of that 7, and we're going to subtract the 3.5. Now notice I'm very careful about how I handle that, and that I put that in parentheses because it is a quantity that follows this minus sign. And then the only thing left to do is start evaluating. I'm going to have to maybe scroll just a little bit here. I apologize for that, but we have to figure out this f of 6. So if I go back to the graph here, f of 6 looks like it's going to be this value of -3, so we'll use him. And then I have, well, 0 times f of 0. I don't really think we need to concern ourselves with what f of 0 is, as long as we know it's something that's continuous, and it is. And I think from the graph you can tell it was equal to 0, and then 7 minus 3.5, of course, it's going to be 3.5. So now you just have a -18 minus 3.5. You put those together, and your final answer could be -21.5. Of course, you would be fine stopping at any of those 3 locations because they are all in its final numeric form that are all equivalent. And I'm not going to talk about f other than just to kind of display it on the screen there for you to look at. But hey, what would a great BC question? What would a BC question be if it didn't have this Taylor polynomial connection to it? So Brian did a really good job of using that particular element into this BC1 question, and certainly we'd like you to try that on your own. I'm going to hand it off to my friend Brian. BC2, what do you have to say about that?
Yeah, so I love that problem that Tony just did because it really does show you how we're connecting the idea from today, limits continuity, to all of AB and then to BC as well. So each one of these FRQs that we're doing, not just today, but this entire week, we're going to see a similar idea. So FRQs that start with the topic as well as other AB topics and then connecting them to BC topics. What a really good practice as you're getting ready for this year's exam. And so before we look at BC2, Tony, I did promise that I was going to show you a quick math trick. So I'm going to spend maybe 1.5 minutes showing you guys the math trick I showed Tony. And when we were in high school, Tony had lots of friends. We didn't know each other in high school. Tony, I think, was graduating high school around probably 1 years old, maybe. I don't know. Maybe like 70, 65. I don't know. Close to that. He's very young, but I like to tease him because he is a little bit older than me. But Tony had friends in high school. He was in a band and all kinds of sports. I was a kid that stayed home and played with numbers, right? So I have a lot of friends. Numbers are my friend, like Parker, right? And so I used to look for different patterns in numbers. And so one of the things I noticed in high school, I'm sure millions of other people have noticed it too. This is not a new discovery. So I think I created something new. You might have seen this before, but I used to think about how can I square numbers like 96 squared, right? So I got 96 squared, and I know now that it's 9,216. And I didn't have that memorized. I just did it kind of in the moment. But I want to show you how we can square numbers that are close to 100 in your head instantly, essentially. If I did like 107 squared, for example, something like that, right? What's 107 squared? Well, I'm hoping it's 11,449. So how are we going to do that? Here's how we're going to do this. Let's say a number is close to 100, like 96. Go back to that example. Figure out how far from 100 is it, right? So 96, how far from 100 is it? Well, it's 4 away, right? Now 4 is going to become a pretty important number because since this number is less than 100, it's not quite 100. We're going to take that 4 and we're going to go ahead and subtract 4 from 96. However far away from 100 it is, let's subtract that. 96 minus 4 is 92. And then we're going to take that same 4 and we're now going to square it. And when you square 4, you get 16, and that's your answer right there. It's kind of crazy, doesn't it? Well, let's see how it works with another example. What if we did something like 94 squared? It's also pretty close to 100. Remember, the first step is to figure out how far from 100 it is. So 94 is 6 away from 100, and 94 is less than 100. So we're going to take that number 6. We're going to go ahead and subtract it again from 94. So however far away from 100 it is, you're going to subtract that again. So 94 minus 6 is 88. And you take that number. Remember how far it was with 6? We take that number and we square it, and those are going to be the last two digits. So 94 squared is 8,836. Now, what about this 107 number? Because that was, again, it was close to 100, but now it was more than 100, right? So if I wanted to do something like 107 squared, the same rule applies. We're going to figure out how far from 100 it is. Well, 107 is still 7 away from 100, right? But it's over 100 instead of less than 100. The first two examples were less than 100, but what happens if the number is more than 100? Same idea, but instead of subtracting 7, we're going to add it. So if the number you're starting with is less than 100, you're going to subtract. If it's more than 100, you're going to add. So 107 plus 7 is 114. But then we take that number and we square it, right, for the end. 7 squared is 49. Now, I will mention, sometimes you have numbers, the further away from 100, a little bit more tricky it is, but what if we do something like 97 squared? Okay, so 97 squared is 3 away from 100. Take 10 seconds and see if you can come up with the answer for that. And you can probably do it in your head, right? Or kind of jot it on paper, and we'll see whether you have picked up on this trick or not, right? So 97 is 3 away from 100. We're going to subtract 3. Since 97 is less than 100, we're going to subtract less than 100. We get 94. And then we have to square 3, and 3 squared is 9. So how do I handle that? Well, when you square the number, it really needs to be 2 digits no matter what. It's always the last 2 digits. So if it's just a 9, we can write that as 09 instead of just the number 9. And so 97 squared is 9,409. So there's the math trick of the day. I showed it to Tony. So now he has the best of both worlds. Now we have friends, music, sports, fun, and he has the things I learned in high school, and I have just only this. But there's your math trick of the day. I'll show you a couple more. When I was in high school and college as a teacher, I love studying numbers, love looking at numbers, I love to kind of figure out patterns. So I think a couple times a week we'll share a little bit of a math trick of how numbers work that maybe will impress your friends. If they don't impress your friends, then you got to find some cooler friends who will be impressed by this. We're moving on to BC2, and we're just going to look again at a couple of parts on this. Not the whole question. We have a whole bunch of parts that we're not going to get to. There's a couple of parts that I want to share to make sure that we are understanding how we can make these connections. So we have another piecewise function h, and h actually has 3 pieces this time. The top piece, notice h is defined by a function of h, which is going to be kind of an interesting part of this problem. The middle piece is this fraction that has some k now that we don't know. And the bottom piece is this rational function 12 over x squared. And part A says find the value of k, that middle piece, that makes h continuous at x equals 2. So notice that x equals 2. These are the 2 branches that we're concerned with. These are the 2 branches that are going to meet together when x is 2. And we talk about the first rule of continuity is, well, first of all, we're not checking to see if h is continuous, right? It's always, be really careful about the wording of the question. The one that Tony did, the one that I did originally was all about is a function continuous at a value. We're not asking that. We're now asking you to find a value of k that would guarantee that it's continuous. So it's a little bit different setup, but the same idea applies that if a function is continuous at 2, I need to guarantee that the limit from the left of h of x in this case is equal to the limit from the right. That's how we're going to make sure that our function is going to be continuous. And we know we have other requirements, but that's going to be the first requirement is the left and right hand limits. Well, the limit as x approaches 2 from the left would be utilizing this middle piece here. So if I go ahead and plug in 2 for x to this middle piece, we're going to get 2k minus 1 on top. If we plug in 2 into the bottom, we're going to get 1 times 4, or just 4. And then for the bottom piece, we're plugging approaching 2 from the right hand side, we're going to get 12 over 2 squared, or 12 over 4, which is 3. So in order for this function to be continuous, this means that my 2 answers have to be the same, right? And so we have 2k minus 1 equals 3. And then now we're just solving this for k, and we can multiply by 4, and then add 1 and divide by 2, and we're going to get just a simple 13 over 2. So if k is 13 over 2, this function is going to be continuous. And we can verify that by checking the limits with k in there and checking the point, but it didn't need us to. Just wants us to find the value of k that will guarantee that. So that's going to be our part A. And I want to look at part B as well, because this question is a limit question. And the limit question, and whenever you see a limit question on a free response problem, your radar should go up and be thinking this is probably going to be a L'Hopital's rule question. And so it doesn't have to be. We actually saw the question on last year's exam on the free response that was a limit problem that wasn't L'Hopital's rule. A lot of students start doing L'Hopital's rule unnecessarily. But whenever you see a limit, that should be your instinct is it might be L'Hopital's rule. And this is a good question because it connects us to this idea of continuity in the sense of to show something's continuous, we have a very specific procedure we have to follow because there's a definition involved. In order to invoke a definition, you have to show all the pieces of it mathematically. The AP exam, one of their goals is to allow you as a student to think and to act like a mathematician. They want to give you opportunities to be mathematicians. And part of that is showing proper notation, invoking conditions, and invoking definitions and theorems properly. And so L'Hopital's rule is a theorem. We call it L'Hopital's rule, but it's really a theorem because it's an if-then statement, right? And so how you write this is going to be really important. So pay really close attention to this. And Tony and I will bring this back up again in the next coming weeks as well, multiple times, because it's one of those areas that seems to be tested on every FRQ or every year, now, but yet students don't quite know the proper notation. So to do L'Hopital's rule, we really have to evaluate the limit of the numerator. This will be h, not f, right? The limit of the numerator and the limit of the denominator separately. So we have to take the limit as x approaches -3 of the numerator, and we have to take the limit as x approaches -3 of the denominator. A big mistake that students make is they kind of just write things like equals 0 over 0, right? That's a big no-no. You can't equal 0 over 0. L'Hopital's theorem actually tells you to evaluate these two limits separately, and if they're both 0 or both infinity or negative infinity, then we can invoke L'Hopital's theorem. But we have to show them separately. So it's really important that we show them distinct like this. So the limit as x approaches -3 of h is going to be h of -3 minus 4. And now I got to go find out what h of -3 is. Well, I'm going to plug into the top piece, and that's the one that's going to include when x is -3. Well, notice the top piece is just another function, isn't it? So h of -3 is just 3 times h. If I plug -3 into here, -3 squared minus 6 just becomes 3. So really we're kind of jumping around because h of -3 is going to be 3 times h of 3. And to find h of 3, now I got to come down to here when x is greater than 2. So it's going to be 3 times, if I plug in 3 into here, it's going to be 12 over 9 minus 4. And if we reduce all of this, guess what? We do get our 0. And the limit of the denominator as x approaches -3 is just going to be 9 minus 9, which is 0. So notice how I showed those two limits separately. That's going to be the first step just to even have a chance to invoke L'Hopital's theorem is by doing those limits separately and not writing just equals 0 over 0 or arrow. This is the proper way of showing it, how you communicate that. So now that we both get 0, we know we can apply L'Hopital's theorem. So now I can just say by L'Hopital's, and then we know L'Hopital's theorem says we can just differentiate the numerator and the denominator. The limit of this function is going to be equal to the limit of the derivative of the numerator over the derivative of the denominator. So h prime over 2x. And in this case, I know if I plug in -3 to the bottom, we're going to get -6. So all I have to be able to do now is find h prime of -3, right? And so now it requires me to have h prime. And we're given a function of h. So we're going to have to do a little bit of side work here to figure out what is h prime of x. I can't figure out h prime of negative 3 without first knowing h prime of x. And so if I take the derivative of these first piece here, it's going to be 3 times h prime of x squared minus 6 times, by the chain rule, 2x. And that's going to be for values that are less than negative 2. I'm going to get rid of the equal sign because I don't know if it's differentiable there or not, but this is going to be a nice chain rule derivative. The middle piece I'm going to leave out for now, and the reason why I'm going to leave it out is because it turns out we're not going to need it for this problem. But if we had asked you to find h prime of x, we would solve all that. And then I also need to find the derivative of this bottom piece. And to find the bottom piece's derivative, I'm going to bring that x squared up and make it negative 2 first. So this derivative is going to be, what is that, negative 24 x to the negative 3, or x cubed. And that's going to be when x is greater than 2. And again, I'm going to leave off the equal sign because I don't know if this function is differentiable at those corner points or not. And so if I want to find h prime of negative 3, I'm going to plug it into the derivative up here at negative 3. And that's going to give me 3 times h prime. If I plug in negative 3 for x, again, we get 9 minus 6 in there, which is going to be just 3 times 2 times x. Remember, x was negative 3, so that's going to be times negative 6 all over negative 6. So now the nice thing is the negative 6 is going to cancel, and all we get is 3 times h prime of 3. Now we got to find h prime of 3. This problem has us bouncing back and forth between these two limits, or these two pieces of function quite often, but h prime of 3 is now the bottom function, right? And so it's going to be 3 times h prime of 3 is right here, and so that's going to be negative 24 over 3 to the third power, or 27. Since this is an FRQ problem, we're allowed to leave it, right? We don't have to simplify our answers, so we can leave it like this. But if you wanted to simplify, I think all of this just becomes what? Negative 24 over 9, which is going to be negative 8 thirds. So the final answer, if you did reduce it, would be negative 8 thirds. Pay more attention to how we set up L'Hopital's theorem, and knowing the notation showing the left limit and right limit separately before you apply L'Hopital's theorem. And don't get too focused on the fact that we have this kind of crazy piecewise function that has bouncing back and forth. That's kind of the top of the difficulty scale of what you might see for L'Hopital's theorem. But Tony and I will give you more examples of these in the coming days and weeks. That way you can keep practicing this proper notation for doing this. So there's a lot more great problems on here. I'm going to leave it at this one. And then if Tony, I was going to kind of make a mention, I think, of BC3. I don't know if I have time to get through examples or not. We might point out a couple things for you guys to try out.
So the BC3 has a lot of really wonderful elements. As you move through it, you'll see that part A mentions about continuity. Very similar to what we did before, but the big key element that's different is the fact that you've got a table of values. So you're going to attack a lot of the same concepts, but in a different environment. And we will say that L'Hopital's rule makes another prominent appearance with this particular problem. And towards the end of it, it looks like you may be doing some use substitution integration. So we certainly invite you to take a look at problem 3. It is the last of the free response questions, so but it does have a lot of parts to these problems have a pretty robust nature to them as they go up to parts D, E, and F. So we certainly would love for you guys to take a look at those. So let's tweet out. Yeah, let's get tweets with Tony here. So what do we got going on here with our AP Teachers Rock hashtag? Well, we're going to recognize the fact that AP Teachers Rock, shout out to my BC teacher, Mrs. Hansberry from Little Rock Central High School. She worked so hard to prepare us for the AP exam, and she teaches us wonderful calculus. So congratulations to you, Ms. Hansberry. And for our AP Students Rock, special message here. I am so proud of how all of my students are working and helping each other. TJ even helped me navigate YouTube to find some attachments. So we want to thank Mrs. McGreevy. Mrs. McGreevy from Spencerport High School, just outside of Rochester, upstate New York, right along Lake Ontario. So thank you very much for that. Go Rangers. And I also want to recognize a young lady who's become a friend of ours, Lydia. Lydia, thank you so much for the wonderful message over the weekend. Lydia is a student who attends the Rift Valley Academy. It's a job Kenya. It's a school there in the eastern part of the continent of Africa. And due to the coronavirus outbreak, she's had to quarantine herself all the way into northern Africa. So she's in Tunisia right now. And Lydia, we just want to send out our thoughts and prayers to you, your family, and of course all of the other students at Rift Valley Academy, and wish them much luck in preparing for their AP exam. This truly is a global effort. We have students watching and joining us and learning with us from all over the world, and we're so excited for that very fact. Once again, the lessons for the upcoming week, all connecting AB to BC. So there you go. If you want to take a real quick peek at that, tomorrow we'll be back on talking about differentiation and integration, and we'll move into some other various topics throughout this week. And then that sets up next week for our problems type week that we'll talk about a little bit later. So again, if you're having trouble with internet access, with equipment access, you can certainly have yourself or a friend of yours reach out to cv.org/tech to get a lot of those issues remedied. And Brian, I think that takes care of us today. It was a great show. Thank you so much for your math magic trick. I thought that was switchcraft at first, but it's a wonderful little tool. And hey, maybe we don't need calculators as much as today, right?
Exactly. And Tony, real quick before you head us out here, stay tuned, students and teachers. This coming week and next week, we got some more math tricks coming your way. And I believe Tony even has, I won't give it away, a guest speaker that is going to be, you should recognize this guest speaker and be pretty excited about it. So stay tuned to that. And I want to echo Tony's sentiments of Lydia, but we get so many really cool tweets, emails, and messages from students and teachers, and we cannot quantify how much we appreciate all the support. And there's a lot of gratitude and a lot of camaraderie. We're all coming in this together. We're so excited and grateful that we're a small part of this as you're preparing for the exam in this very unique situation that we find ourselves in. So thank you guys and girls for all of the amazing, just emails and notes of support. Tony and I know we appreciate them, and we're saving them because that's what keeps us going on those nights that we're working until 3 o'clock in the morning trying to prepare for these lessons pretty much every day.
All right, till next time. Stay safe, stay healthy, and keep learning.
AP Calc, yes, AP Calc. Welcome you to AP Calc, yes, AP Calc.
Calculus. Taylor Polynomials. Infinite series. Differential equation. Calculus. Taylor Polynomials. Infinite series. Differential equation.
Well, good morning, everybody. We are so excited that you are joining us today. Today we're going to be looking at differentiation and integration as we continue this week's theme of connecting AB to BC, where each day we look at an AB topic from the curriculum and then do a quick review of that and then make some connections with that topic to other topics in AB, as well as connecting that to topics on the BC exam to help you get prepared for the 2020 AP exams. As always, our materials should be in a little link underneath our videos. If you click on the link, you'll be able to find the handouts from today with a whole bunch of problems that we'll be doing today, as well as many problems that we want to get to. And the solutions are posted each evening around 9 p.m. Eastern time. So I am, as always, joined with my co-host, Tony Rickard. Tony's a teacher at Avon High School, and I'm a teacher at Speedway High School. Both of us are from Indiana. And Tony and I have been doing these sessions now for about 3 weeks, and we're excited that during the review times we're working together. And it looks like, well, Tony might be having some technical. Tony, I don't think your camera's on. Tony,
What does this button do? Start video? Start video?
Grover.
Is this on?
Yeah, Grover, you're way too close, man. Yeah, scoot back a little bit. There you go. There you go. Grover. Hello, Grover. I was expecting Tony this morning. What are you doing here?
I'm traveling to talk about my book. The monster at the end of the book Have you read it?
Yes, I have actually. And Grover, it's really odd that you're here, really unexpected, right? And I know a lot of calculus teachers who are watching, and probably a lot of calculus students have actually read your book. So I'm sure they're really excited that you're doing a book tour and walking around and meeting with them. But is that even okay? Aren't we on like a social distancing? Is that safe to be going on a book tour right now?
Grover, have secrets. I'm a Muppet.
Oh.
Antibodies.
Yeah, I got you. Okay, that makes a little bit of sense, I guess, right? Well, Grover, I'm surprised. I'm a little bit shocked that you're here. I'm not sure what to do with that, but Tony and I were going to be doing a calculus lesson today. Do you think maybe you want to stick around and try your hand at that and maybe teach us calculus today?
Grover, try. Yes, yes.
You're good at calculus?
I think so.
Well, here's the beginning. Tell me if you can handle this. If you can't, then maybe we'll get a nice lesson from Grover this morning.
Let me see. Grover doesn't know how to do this. Grover doesn't know calculus.
Oh, Grover, don't be sad. I'll tell you what. If you get a little bit of time before your next book signing, can you stick around maybe and then let Tony teach you and let us maybe Tony and I together can teach you and maybe you can actually learn some calculus today.
Yes, Grover, like that very much.
Well, that's awesome. That's perfect. Do you think maybe you can? Is Tony around there? Have you seen him anymore?
Go get Tony. Tony.
Oh, we lost Grover, I think. Hopefully you can find Tony. I don't know.
Here I am. Hey, thanks, Grover. Hey, no problem. Just don't touch that. Just I say what. Sit right there, and Brian will teach you calculus just like the rest of the folks. How's that? Oh, sorry about that. I let him near the control station when I was going to fill up my cup, and who knows what would happen. All right. So where are we? Derivative rules. Is that where we're at, Brian?
Yeah, I think that's where we're going to start off. I thought maybe we're going to get a special lesson from Grover today, but I'm glad that you're here. I was a little bit nervous.
Well, he's got his pencil. He's got his handout, so he's ready to go. So what do you say we take a look at these derivative rules? And we've got these classified into tier 1, tier 2, tier 3. And the tier 1s are the must know. And those are the ones that we definitely want to go into the AP exam having quite a bit of confidence on. And the tier 2, helpful to know. I'd say any good calculus student would be a great idea to have these under your belt. But any given year, you might see maybe a couple of these show up every now and then on the AP exam. This year could be an exception, could not be an exception. We just have to wait and see. And then the tier 3, the honorable mention. Those are the guys that, hey, as any calc student, it's great to know those, but they're very, 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 very unlikely to appear on any year's AP exam issue. So let's go ahead and start off with some quick check. How about that? We've got quick check 1 here, and let's take a look at part B to begin with. So we have some values in the table, and the question reads: the functions f and g are twice differentiable for all values of x. Selected values for f, g, and their derivatives prime and g prime are shown in the table. So if we take a look at part C, the thing that we want to kind of capture here is the strategy by which we're going to take this derivative. And we have c of x defined to be f of g of 2 of x. So a lot of stuff going on there. And this is just a tailor-made chain rule problem, but it's got even a little bit more of a twist to it because of the layers of the function that we have. So if we take this derivative, c prime of x, what we have going on is that we first of all have to take the derivative of the outer function. There's so many analogies to these, peeling an onion and using charcoal pops or M&Ms, peanut M&Ms. Maybe I'll use that analogy when we're finished here. But if we take that derivative of the outer function f and we have f prime, all of the inner function stays the same. You can almost think of that outer function as like being the candy shell of the peanut M&M. That's the first thing that you're going to taste. That's the first thing that's going to contact with your mouth. All of the stuff that's inside that M&M is not going to change, right? The g of 2x is going to be the same. And then we would multiply that by, now we're into that chocolate around that peanut, right? The middle part of that. So we would take that derivative of g in this case, whereas the peanut, the 2x, is going to stay the same, right? He's still in there. And then finally, we get to the end and we can take the derivative of that inner part, the 2x, which in this case is going to give us 2. And now we have completed this. Well, sometimes we refer to as maybe a double chain rule type of derivative. So next we can go ahead and plug in our 2 for x. And upon doing that, we would get f prime of g of 4 times g prime of 4 times our 2. Now we wouldn't be finished yet. We wouldn't be able to get full credit for this problem until we evaluate those particular functions. So g of 4, we go to the table, we end up getting a 1. I'm sorry, g of 4 is a 0 rather, so f prime of 0. And g prime of 4 is going to take us to the bottom row of the table, and that gives us a negative 2. Make sure we draw down that up 2. And then for our f prime of 0, we're going to slide across this row. We see that f prime of 0 is 3. So it looks like when all is said and done, we would have 3 times negative 2 times positive 2 in this case, I believe. And that would give us a negative 12, unless I made a terrible mistake. I think that's right. Grover agrees. Okay, so Grover, you're learning good. All right, let's go ahead and take a look. Why don't we move down to D? I think Brian and I talked about this would be a pretty good one to take a look at because it's going to utilize a very popular derivative formula, right? The derivative of the natural log of u. And if you want to flip back to your tier 1, tier 2 honorable mention chart, you'll see that this is definitely in that first column, and that the derivative of the natural log u, sometimes we think of it as u prime divided by u. So if we go about our business and take the derivative of n of x, so get n prime, the u in this problem is going to be this f of x. So by virtue of that formula, we can call this derivative u prime or f prime of x over f of x. Now all that's needed to be done is we insert 4 for our x, and we have something like this. And then at this point, we just can go to our chart and see what we got. F prime 4 looks like that's going to be a 15 from the chart, and then for the f4, you always have to make sure that you're going to the correct row. And 15/5 would be an unsimplified correct answer, but if we simplify it, we would get this nice value 3. Right? We encourage you to take a look at the other 2 problems in quick check 1 that we didn't check out today. Let's take a look at quick check 2 and maybe look at just a couple of more here. A couple of different things going on in quick check 2. First of all, we are given a pair of graphs. So it reads the functions f and g are continuous on the closed interval negative 3 to 6, and the graphs of f and g are shown in the figure above, and each consists of 3 line segments. So looking at h of x defined as f of x squared, and we're asked to find h prime of negative 2, we go about our derivative and we develop our strategy again. And our strategy is going to be that of a chain rule because we definitely have a composite function here. Outer function, this function called f, the inner function is this value or this expression x squared. So if we take the outer derivative f prime, keeping the inner part the same, right? We have f prime of x squared, and then we take the derivative of the inner part to get 2 times x, and then we can finish it up by replacing the x with negative 2. And negative 2, of course, squared would be a positive 4. 2 times negative 2 is negative 4. And then we would go to our graph. Now the graph is set up so that we're looking at a graph of f of x and g of x, right? So if we want to find f prime of 4, so we have to follow along this particular path of the f graph, and right here's where 4 is. But you want to resist the temptation to call that 1, right? Because that would be f of 4. We instead have to look at what the slope of this piece of this graph is going to be, which at this point is down 1, right 1. So that would be a negative 1 slope. And of course, when that's multiplied by negative 4, we get a result of positive 4. Okay. Let's do one more here before we turn it back over to Brian. Let's take a look at part C, because part C for the first time here today is going to have us exercise the usage of the product rule. And we have our p of x function now defined to be f of x times g of x. And we're going to evaluate this for p prime 4. So if we take the derivative in general of p prime of x would equal, you can set up your product rule a couple of different ways. I'm going to choose to take the derivative of the first function times the second function, and then we add to that the first function multiplied by the derivative of the second function. And of course, a lot of textbooks might switch the order. The commutative property is alive and well in this particular problem with the product rule. Not so much in the quotient rule, so you have to be careful about that. And we insert 4, and we have f prime of 4 times g of 4 plus f of 4 g prime of 4. And we again read right from the chart. I think f prime of 4 we've been there just a moment ago. We have that negative 1 slope. And for g of 4, boy, talk about switching gears here. Not only do you have to switch to the other graph, but you also have to realize you're looking straight at the y value now, so negative 2. And then for the f of 4, we're back up here looking at the value on the graph, positive 1. And then for g of 4, well, we get down here and we realize, oh, the slope to this piece of the graph is just going to be a 0. So when we simplify that expression, we get positive 2. And it's very possible that throughout the year you've seen instances of product rule, quotient rule used in this fashion with charts, maybe with graphs. Teachers out there, it seems like we can never have too many of these. So you've got an excellent collection of problems problems that you can still inject into your curriculum in the future. But it's a really wonderful way to test these concepts, again, without giving the students that analytic approach, that algebraic piece that they can manipulate so easily with a calculator, which we know is something that's just not going to happen on this year's AP exam. So, and I think Brian's now going to take it away and do a few other quick checks beyond, I think, quick check 4, if I'm not mistaken. Is that right?
Absolutely, Tony. And so we're going to make a quick transition now to integration. So Tony did a great job doing a nice refresher on some of our derivative rules, the main ones. And then especially, I hope, and Tony mentioned this, but I want to make sure that you heard what he said. It was so apropos for how this exam is going to be this year that we're going to see a lot of graphical and tabular questions like Tony just looked at, because that's how we can really check your understanding during one of these take-home style tests when we know that you have access to Google or calculators or even those apps on the phones now that will solve problems for you. These are the kind of problems that are going to be not able to get around the math. You're going to have to show that you can do these problems, and those other resources aren't going to give you the answers like your own understand will. So as we do that, we're going to keep that same mindset, and we're going to look at some integration rules, and then we're going to take a look at a couple examples here where we're going to see how integration might appear in a lot of different ways. I always love integration because I always feel like it's like a detective story to me. I'm trying to figure out the best approach. Derivative rules are a little bit more straightforward because you recognize a rule and you apply it. Whereas integration, since we're doing anti-differentiation, it's a little bit more problem solving in the beginning, but the calculations are a lot easier once you identify what type problem it is. And so just like before with integration, I like to break up my problems into 3 tiers, and I call the big 5 is tier 1, because if you look at past exams, the actual integration formulas that you have to know, about 90% of them, of the problems in AP exams, come from these 5. And if you know these 5 integration rules, you can get through the vast majority of actual AP questions involving integration. And the nice thing is they're just the same exact formulas as our derivative rules. And I can put them in the same order. So if you know your derivative rules, the antiderivatives are just going in reverse. So these are going to be the big ones, recognizing those. And then tier 2s are what I call helpful to know, kind of mentioned before. You might see a question on there. They're not as common. And then tier 3, you're probably not going to see a problem like this on an AP exam, but certainly in college, Calc 1 or Calc 2 or Calc 3 course might expect that you have these known for future coursework. So the big idea with integration rules is this U substitution, right? Notice I didn't use any X's in any of these problems. They're always U because the questions never look this simple. That's the problem with integration. And it truly is anti-differentiation. Derivative problems always start out kind of simple and clean and nice, a very kind of small problem. And then when you apply the derivative rules, they expand and sort of get uglier, right? Whereas integration is the opposite. The problems look expanded. They look kind of ugly and complicated in the beginning. And our job is, before we even start the calculus, simplify, reduce, and clean up the problem so that we can apply one of our basic integrations. So when you're doing integration, don't be so quick to start the calculus part of it. Start thinking about the structure of the problem. What do I recognize when I do U substitution? How do I clean this problem up so it becomes a little bit easier to handle? So we're going to look at several different examples. And just like with the ones that Tony was doing with us, you're going to see 2 problems per page, and we're going to just do 1 of each page. So you can go back later and try the other problems as some additional practice as you're reviewing these ideas. So quick check number 4 is a table problem. And it says we're integrating here on the left-hand side the integral from -1 to 2 of this f prime of 2x e to the f of 2x. And my first instinct was, oh man, if I flip back to that previous slide, that wasn't my big 5. You know, Brian, you told me these big 5 are going to be the main 5 problems. You should know this doesn't look like one of those. It wasn't in tier 2 or tier 3. This is what I mean by cleaning the problems up first. On the surface, they look ugly, they look complicated. But if you step back and think, okay, what type of those big 5 problems do I notice? And I notice this e in the problem, which makes me think this is going to be of that form, the integral of e to the u du, right? That's one of the big 5 that it is. And so we're going to do some U substitution. So whenever I see like an integral involving e, typically the exponent of e becomes my U substitution. So here, I'm going to do a little bit of side work. I'm going to say, well, then I'm just going to trust the process, right? I don't quite know how it's going to turn out. But what if I set the exponent of e equal to u? And then when I do U substitution, I immediately have my students find du or u prime. You might call it different things. But we're going to call it du. I was doing derivatives earlier, so I was calling things u prime. And then the derivative of f of 2x is going to be 2 times f prime of 2x dx. And every teacher, I feel like, teaches integration a little bit differently. So if this looks different than how you learned it, I think Tony hit the nail on the head yesterday when he said, if what you're doing is working for you and you're good at something, certainly don't change what you're doing. There's different approaches. This is how I teach it. So don't worry if it's a little bit different. I make my students, once we have our du, we don't go on until we make sure in the integrand we have exactly what du equals. I have to have this 2 f prime of 2x dx. I've got everything I need. I've got my dx here, my f prime of 2x. I'm just missing the 2. Like, I wish there was a 2 in this problem. And so I like to just say we're kind of the god of numbers in math, right? In calculus, we're kind of the god of numbers, meaning if we wish there was a number there, we can create one into existence as long as we balance out our universe, our math universe, by canceling it out in front. So if I wish there was a 2 there, poof, we can create the 2 that we need as long as we keep balance by putting a 1/2 in front. And I always say we're the god of numbers. We're not the god of variables, meaning if we're missing an x for our U substitution, we don't get to create an x and then divide by an x out in front. It only works with constants, right? Using our properties of integration. So by doing this, I've now got this in the proper form. And so we're going to rewrite this in terms of u. So if I rewrite this in terms of u, I have e to the u. And remember, all that other stuff I underlined in blue, that was just e. So all this ugliness became something very simple like this one right here. So now what we have to do is make sure that we change our limits as well. You notice I didn't write those limits on there because the -1 to 2, those correspond to x's, right? Every integration problem has 3 pieces, right? Every integral has a differential at the end that tells you what variable you're integrating with respect to. It has an integrand, which is the expression that you're integrating, which has a variable, and then it has limits, right? And all 3 of those things have to match up, meaning in this case, all 3 of those are in terms of x. So if I'm going to rewrite my problem in terms of u, we've got to make sure we remember to change those limits. And on an AP problem, a lot of times what my students will do is they'll keep those -1 and the 2 on there, and then they'll just convert things back to x when they're done. And that's a fine idea. The problem is if you write -1 and 2 on there, you've now told us that your limits for u are -1 and 2. That's a false statement, and there's going to be a penalty on the scoring of the exam because you've written something that's not true, even if you convert back to x later on. So what I like to do is just go ahead and change those limits to be in terms of u, and we can change those limits by using our formula here. U is equal to f of 2x. And so when the lower limit was -1, that means that u is going to be f of -2. If I put -1 in there, and then going to our table, we can see f of -2 is just 1, and the upper limit when x is 2, we get u is f of 4, and on our table f of 4 is just going to be 0. And so my limits here, my lower limit becomes 1, and my upper limit becomes 0. And notice how I put the lower limit as 1 because that's what the lower limit became, right? Even though these are sort of what we call flip from how we normally like to have them, like to have the lower limit on the bottom typically, we have to put them in the corresponding place. If you want to flip these around, we can do that using another property by making the integral negative in front. But if we're going to be applying the fundamental theorem of calculus, guess what? We don't have to flip those limits, right? The fundamental theorem of calculus works no matter how the limits go. So I'm going to leave my limits like that for now, and then we're going to integrate this using one of our 5 rules. So the integral of e to the u, now that we have it in proper form, I love e to the u because the integral of e to the u is just e to the u. And then my limits are going to be from 1 to 0. And as always, we plug in the top limit first. So we're going to get 1/2 e to the 0 minus 1/2 e to the first power. And on AP test, this is numeric, meaning you could type that into a calculator, right? There's no variables there. I know a lot of times students think e is a variable, but it's just a number. So you can leave your answer like that. If you wanted to simplify, you could. It would just be 1/2 minus 1/2 e would be another acceptable answer. So that would be a good example of U substitution. If we jump to another problem here on the same quick check, but we're going to part C, so same exact table. It's a different approach, right? We don't have one of our 5 forms. We don't have any e's, cosines. We have this function f double prime of x in the problem. And my first instinct with any integration problem, whether you're in Calc AB or in Calc BC, is look for those parentheses, right? When you see things in parentheses, that's usually a sign that you might be able to use U substitution. I always check that method first. I think sometimes in Calc BC, we get so focused on these BC ideas, like integration by parts, right? That we always want to make everything integration by parts or something like that. And so every time we see a product, we try to take that approach when the U substitution is still going to be a very, very common technique. It should probably be our first thought no matter what. And so if I look at parentheses, the things inside the parentheses are usually going to be what we set equal to U. And I always do a quick check to say, well, if the inside is U, is the derivative of that floating around on the outside anywhere, right? So if U is x squared plus 1, U prime or du would be 2x. Well, there's my x right there, right? So as long as you have the variable, we can fix the number, right? We don't always have the right number. Remember, we are the god of numbers, so we can create the numbers we need to to make the problem work. And so I'm going to go ahead and try u substitution again on this one. So we have u equals x squared plus 1, and that means that du is going to be 2x dx. And just like before, I need to make sure I have my du in the problem before I go any further. There's the dx that I need, there's the x that I needed, and then I'm just missing the 2 in front. So if I put the 2 there, right, I can squeeze it in there, multiply by 2, then I can multiply in front by a 1/2, because if we try to create a number that we need, we're going to have to offset that product, right? We're always allowed to multiply and divide an integration problem using our properties of integration. So now that we have this, we can go ahead and rewrite this problem. So this is going to be a 1/2 in front, and we're going to write it in terms of u. So we have f double prime of u, and then notice everything on the outside, just like before, just turns into du, and then we still have to change our limits to be in terms of u. I always think it's helpful to make everything in terms of u. If you're doing definite integration like this with u substitution, change those limits, and I'm going to encourage you not to go back to the x version of those, right? A lot of students will convert things to u, they'll integrate it, and they'll convert it back to x and plug numbers in. Remember, u is the simpler form, so keep it in terms of u. It makes your math a lot easier on the back end. And so if I go ahead and rewrite this, the lower limit was -1, so if I plug that in for my x value, my lower limit is going to become 2, and my upper limit was 0, that's going to become just 1. So my lower limit is 2, my upper limit is 1, and now we're able to go ahead and integrate this using the fundamental theorem. So the integral of f double prime, notice in the table, we have a row of f prime. Sometimes students, this is always like a big trap, right? We do all of this front work using u substitution, that when we finally convert things to u, we feel like we've done so much work that we try to just plug those numbers in. We want to just plug the limits in, thinking, oh, I've done a lot of work, I should be plugging things in about now. But remember, we haven't actually done any calculus yet, right? We have to integrate this function first, and so don't try to plug numbers into there before you integrate. And so the integral of f double prime, this is a nice conceptual example because it's not one of those tier 1, tier 2, or tier 3s. It's just understanding how our charts work, right? What's the antiderivative of f double prime? Well, that's just going to be f prime, right? And then we're going again from 2 to 1. So we're going to have 1/2 f prime of 1 minus 1/2 f prime of 2. And notice, again, I didn't have to flip those limits, right? Because the fundamental theorem takes all that into account. Now, you certainly can flip them. If you want to flip them and put a negative and 1/2 in front of your answer, you're going to get an equivalent answer as doing it this way. Now going to our table, we have to have some numerical values before we're done. So 1/2 f prime of 1 is going to be 1/2. And so the table carefully, f prime of 1 is right there. So that's going to be -4. And then minus 1/2 times f prime of 2, and f prime of 2 is 1. As soon as I'm at this step right here, we can leave it because this is a numerical answer. There's no need to simplify. But Tony and I are math teachers, and it's really hard for us to not simplify things. In my class, I've heard Tony say this too on the air, as well as some workshops we've done together. We catch ourselves saying things like, we don't have to simplify this on the exam, so we can leave it just like that. And we kind of notice a brief pause, and then we can't control ourselves. We have to go back and actually simplify. Like, okay, I'm going to do it anyway. But you don't have to simplify it on a time test, a 45-minute test. We know this year's test is 45 minutes, and we also know it's going to be a full 45 minutes, meaning they want to give you a test where you have a chance to work the entire time. So anytime you don't have to simplify, it might save you a few more seconds to think about some of the more challenge problems that come up. So moving on to quick check number 5, these are going to be some graphical examples here. And what I would like to do is skip we're going to do part A, but I want to skip this and move on to part B, only because Tony has a really good FRQ problem to tie a lot of this together. So I want to make sure we get to that and possibly even a part of the one that I was going to do at the end. And so I want to show you one graphical example. I'm going to go through a little bit more quickly now because we've done u substitution several times. I see my parentheses, and so my natural instinct, hopefully you see it too, is that the u is going to be whatever was inside the parentheses. And then immediately once you find u, I just figure out what the derivative is of that expression or that equation, and I get 2x dx. I look at my problem and I say, hey, do I have a 2x dx there? I got everything I need but the 2, so I'm going to put the 2 there, and I'm going to put the 1/2 in front. As I'm looking back and doing these problems, I'm realizing I must like that 2 and 1/2 combo because all the problems we've done have that same fix, right? I won't. That's not a general rule for AP exams. And then now that I have this, I'm going to rewrite this in terms of u. That just becomes f of u du, and then my limits, again, if I replace my limits, the lower limit 3 is going to become 6 because 3 squared minus 3 is 6, and my upper limit of -1 is going to become -2. -1 squared minus 3 is -2, and we get -2 up here and then 6 down here. And then this is the one case where I encourage my students, you don't have to do this, but I see a lot of mistakes on exams and with students if they don't flip the limits in this case. And so why was it on the first two examples we did, I didn't flip those limits when the lower bound was bigger, right? We like to have that lower bound smaller normally, the upper bound. But when you're applying the fundamental theorem, when you integrate and plug those numbers in, it doesn't matter what order they're in. As long as you do the math correctly, you get the right answer. In this case, we're not going to apply the fundamental theorem. We can't actually integrate f. We're not going to integrate f because the integral of f would be like capital F. Well, I don't know what capital F is. What we're given up here is a graph of regular f, right? And so if I integrate this, it becomes capital F. I'm not sure how to find that. However, the integral of f, if you're given a graph of f, remember the integral of a function is just going to be the signed area between the function and the x-axis. And so the integral of f is just kind of the area model of the graph of f. So whenever I'm doing the area model, not the actual fundamental theorem, that's when I like to make sure my limits are in the proper form because I like to always go from left to right. And I know that a lot of teachers will teach that you can go from right, you can go backwards, it's fine as long as you make your answer negative. All that's fine. But what I found is you start going backwards, you don't flip those limits. You have to make your whole answer negative. Plus you have some parts of the area that are negative. You have all these negatives and negatives, and it gets a little bit confusing. And a lot of mistakes happen. So I like to make these examples the lower limit and the bottom smaller. So I'm finding the area starting at -2 and I'm going to 6. The integral of f from -2 to 6 is just that signed area. So we're going to have a -1/2 in front. And if I go ahead and do this, remember this part right here is below the x-axis, right? It's a part of the graph below. That's why I mentioned the signed area. So I know the area is positive, but the integral is the signed area, meaning if the part of the area is below, it's going to give me a negative integral. And then the second part of the area is above the x-axis, and we get a positive 12. So in this case, I am going to leave my answer like this, so I don't have to deal with simplifying it on live YouTube and making a mistake. So Tony, I think you're going to walk us through a couple practice problems on one of the FRQs. Is that correct? That's going to tie some of these ideas together.
That is correct. On our BC1 and BC2 questions that you have access to, it looks like 4 of the parts are going to tie into AB topics specifically, and then 2 of the parts will tie into a BC topic. And I think I'd like to jump ahead here to part C, if that's okay, and read the stem here very quickly for BC1. It says the function f is twice differentiable in the closed interval -5 to 10. The graph of f is given. We also know that we have horizontal tangents at -5, -1, 2, 6, and 9. And the areas bounded by the graph of f of x and the x-axis are provided in the figure. The twice differentiable function h is defined as follows, and it is known that f prime is 0 is 4. So a lot of stuff going on there. We just have to use that information as it occurs in our problem. So for part C, we're going to define k of x to be h of x over 2x, and we know that the integration from 0 to f of x is 5, and from that we want to find k prime of 4. So finding k prime of 4 pretty much takes us back to this beginning function, and that we want to take its derivative. So we developed the strategy by which we're going to do that, and we can see that this is certainly a quotient. So we'll use that idea of the quotient rule, and I will start it off by taking, say, the derivative of the top multiplied by the bottom. Those can be reversed if you like to do the high d low minus low d high, and then make sure you put a subtraction in, and then we have the numerator multiplied by the derivative of the denominator. And of course, all of this would be put over the denominator, which in this case is 2x quantity squared. So it seems like a very easy start to the problem. Just know the quotient rule and move on from there. And then let's go ahead and plug in 4 for x. And so all these x's are going to be changed to 4s, and I think I might go ahead and do any kind of arithmetic that I see. And let's see, in the denominator, we could probably go ahead and take care of this. 2 times the 4 would be 8, and once we square it, of course, is 64. So now really the only thing that's holding us back is finding h prime of 4 and finding h of 4. So let's look at h prime of 4 first. So we go back to this function defined by this integral h of x, and we see that, oh, well, if we want to find h prime of 4, we first of all have to consider what is h prime of x. And we've been here before. We've had a couple of problems like this in some previous videos, but we're going to use one of our fundamental theorem of calculus ideas, and that would allow us to take this upper boundary and then replace our independent dummy variable t with that. And that would give us f of x over 2 in this case. But because that upper boundary is something a little bit more significant than just an x, we are forced to take his derivative and multiply by using that chain rule. And that works every time as long as your lower boundary is some kind of constant. All right, now we're supposed to figure out what h prime of 4 is from this. So let's say if we enter a 4 for this x over here, we have 1/2 times f of 2. And f of 2 can be read from the table, or I'm sorry, from the graph. If I just scroll up a little bit, here's 2, here's our function f, and it looks like we have a y value of 4. So 1/2 times that 4 would be 2. So we can certainly replace this h prime of 4 with a 2, and of course there we get 16. So this is kind of what I have so far here. I'm now waiting on figuring out, well, what's this 2 times the h of 4 going to be? And that brings up another very interesting situation. So we figure out, all right, well, what is our h of 4? I'll kind of work this off to the side, and we see that, well, here's our function h of x defined by this integral. All that we're needing to do is replace the x's with 4. Seems easy enough. So we do that, and we now integrate from -2 to +2 of this function f of t. And as Brian indicated earlier, we just can't integrate f of t. We don't know what his antiderivative is, but we do have this wonderful graph of that, and we have some very powerful information about the areas. But there's a little bit of a problem here. If we try to integrate from -2 to +2, well, finding that definite integral, that signed area from -2 to 0 is pretty easy. But boy, do we have a hard time figuring out what this area is going to be without knowing the equation of that curve. And you want to use the idea that you have this information, the integral from -2 to 0, at your disposal. And well, you would think that this piece of information would get used for something if it was mentioned in the problem. And that's where we're going to be able to tackle this problem. We're essentially going to use an additive integral property that just says, all right, if you want to integrate from -2 to 2, go for it. Just start from integrating from -2 to 0, and then add to that the integration from 0 to 2. Just pick up where you left off and finish up your interval there at an upper bound of 2. And so we can see that the first definite interval gives us a signed area 2.5 but below the x-axis, so that's -2.5. And then we use the idea that the interval from 0 to 2 is +5. And of course, that's going to be +2.5. Now, if that is our h of 4, once we multiply him by 2, that of course gives us 5. If you don't want to simplify, that's fine, but it's not very difficult to get that 11 numerator. So I really like that problem. It does throw in a lot of different obstacles for the student to overcome to piece this solution together. And let's go ahead and look at one very quick BC question. I'm going to look at BC one problem. How about problem F? A few days ago, we had a little conversation about arc length, so we're kind of doing the same thing here with a slightly different environment. Set up, but do not evaluate an integral expression in terms of f that would give the arc length of the function h from 0 to 12. So if you remember our arc length formula, we could say L or S or whatever you want to call it, and it sets up as a definite integral over some boundaries that not all the time are given, but many cases they are. So there's nothing that we really have to do about that. We just know we're going to integrate from the 0 to the 12, and we know that the formula is the square root of 1 plus the function's derivative squared, right? And the function's derivative here is going to be h, right, or h prime. So we have to concern ourselves with what is h prime of x. Well, if you recall, we just did that a moment ago, right, in our part C. So you can just borrow that result, which if you remember was f of x over 2, and then we multiply by the derivative of x over 2, which is 1/2. So if you can just place that inside that integral and square it, you've got the result that you want. You can write it a variety of ways. Just want to be very careful. Let's say if we square just that part, and then for the denominator of 2, we can actually do the simplification for that square. That might be probably the most concise way to write this final answer for just the integral set, right? And I think at this point, Ryan, you're going to take some parts of BC2 and discuss them.
Yeah, we're going to go through just a couple of quick parts on BC2. And Tony, this is a miracle because we're actually pretty close to being on time. So I'm not going to talk for 5 minutes now just to waste that time and make sure we try to push past the boundaries. But we're doing well on time. So as a reward to all the students and teachers, at the end of our lesson, I've got a special surprise for everyone, introducing a new twist to our segments possibly. So stay tuned to the end. We'll get that to you. So since we're on time, we can do this. So this is BC2, another FRQ. And just like Tony mentioned, it's got several different connections between A, B, and BC. Really good practice problems to get you ready for the exam. So we say this every single day, but we cannot stress enough how valuable we think doing these FRQs that we're sharing with you will help you on this year's test, any exam really, but this year's test in particular, because we write these questions, we really are trying to come up with problems that would neutralize calculators, Google apps, and things like that. And so these are, for example, they're always unique, right? So you won't have seen these problems before. You might have similar problems in class during the year, but you haven't seen these problems before, so it'll give you a really good experience what the exam might look like. And so this is BC2, and I'm going to kind of skip past part A, but you can see how this connects to what Tony did in the beginning with some product rule. And we're going to have product rule with a little bit of chain rule involved, kind of a mixture of 2 rules there. But I want to briefly look at part B, just to get us a little bit more practice with the idea of chain rule, recognizing compositions. And so I want to find k prime of 2. Whenever the AP exam says find k prime of a number or f prime of a number, it's always a really good idea to just find the derivative of x first, right? Don't worry about plugging that number in until you have an equation for k prime, right? So I write this down. So k prime, we're going to use the chain rule. We take the outside derivative and we leave the inside the same, and then we multiply by the chain rule of the derivative of the inside, which in this case would just be f prime of x. So now we have a nice equation for k prime, and we can very quickly find k prime at 2 by just plugging in 2 for our x values. So we have g prime of f of 2 times f prime of 2, and then we're going to go to our table and find some of these values. The first thing I need to find is f of 2. So looking at the table, there's my f, and here's 2, and we get 4 for that value. So we get g prime of 4 times f prime of 2. And I think the biggest mistake that Tony and I probably see students make on these problems is they just go too fast and they read the table too quickly and they grab the wrong number, not because they don't understand the math, because they just went too fast, right? So make sure you're pulling the correct numbers. Or we see a lot of students that see this composition and they treat it like a product instead of a composition. Make sure you realize the composition is going to be a chain rule problem. And then we have g prime of 4 going back to our table is just going to be 2, and then f prime of 2 is just going to be 3, and then 2 times 3 is 6. And so k prime of 2 in this case is nice and easy as 6. This was a pretty straightforward computation problem. But think about some other twists the College Board might give you on the exam on this exact same type of question, because remember the College Board wants to see it's not just that you can compute things, not just that you can do some calculus procedures. They want to make sure you really understand what it is you're doing. Sometimes we get so caught up in formulas and algorithms and procedures, we don't spend enough time to step back and think what we found, right? So one application of k prime, they might ask this question some different ways, right? What if they had asked, find the instantaneous rate of change of k at x equals 2, right? Instantaneous rate of change is kind of a verbal way of asking for k prime. Or what if they had said, find the slope of the tangent line to k at x equals 2. Remember, the derivative of a function is equivalent to the slope of the tangent line of that function, right? So a lot of ways they might ask that problem, you have to make sure we understand they're not just going to always tell you find k prime. They might use some words, and then you're going to have to connect that to finding what k prime is. So we're going to jump ahead, and I'm going to look at the last example today, one more integration problem. We did a derivative, and now we're going to do an integration problem with this table. I really like the problem because it's a BC integration problem. How I know it's BC? When I see that infinity symbol on the top, I know it's a BC special type, right? We don't have to deal with that in Calc A, B with integration. That's an example of an improper integral. Remember, our fundamental theorem of calculus, the way it works is we have to have real numbers on our limits. Infinity is not a number of real numbers. We can't use the fundamental theorem. Now, my students always point out to me, but if I do it and just plug infinity, I still get the same answer. That's because you're understanding what's happening, but your notation, technically, you're not using the theorem properly, and so you're not going to be having proper notation, which means you're not going to be eligible to earn all points. And so remember, when we see an infinity symbol as a limit, we have to write this using a limit notation, and we use that, p or some other variable. We say, well, let's take the limit of p approaches infinity of this integral. And we're going to approach this integral where p is a real number now, right? It's kind of it feels a little bit like smoke and mirrors sometimes when you say that you're doing it this way, but p is a number. And once we find the integral with a number, then we can apply a limit to see what happens as that number approaches infinity. So we are going to have to do some u substitution here. We have some parentheses that always becomes u sub. U is going to be 2x, and then du is going to be 2 dx, and then a little bit of a quick fix here is going to give me a 2 here and a 1/2 in front, how we did before. There's my favorite, 2 and 1/2. Keep that in mind for future question, right? And then I'll keep using 2 and 1/2. And then if I apply this in terms of u, we're going to have the integral with 1/2 in front of g prime of u du. And just like before, we really do need to change our limits again, right? And so if u is 2x, my lower limit just becomes 2. And if upper limit is b, I plug it in, we're going to end up getting 2b up here. And then we're going to apply our integration techniques. We have the limit as b goes to infinity of 1/2. My infinity sign became an 8 magically. 1/2. And then what is the integral of g prime? Well, we could do the fundamental theorem. Integral of g prime is just g, and we're going from 2 to 2b. And notice how I'm keeping this limit every step of the way. And what we're doing is I'm just going to plug in. We're going to evaluate the same way we would any other problem. We're going to plug in the upper limit. We're going to plug in the lower limit. And then once we do that, then we're going to apply the limit, right? And so here, if I try to plug in infinity, I end up getting g of infinity, right? It's going to be a 1/2, and I'm going to have g of infinity. Well, how are we going to know g of infinity when that's nowhere on the table? And that's where this stem comes in. X is greater than 0, and it says g has a horizontal asymptote of y equals 5. Remember, when you have a horizontal asymptote, that means the limit as x goes to infinity or negative infinity of that function approaches that value. Well, we know that we can't take the limit as x goes to negative infinity because our domain is for positive numbers and 0 only. So the only way to have a horizontal asymptote is if the limit as x approaches infinity of g is 5. So we have to make that connection between horizontal asymptotes and limits at infinity in this case. So here, I actually can evaluate this, and so we're going to get 1/2, and then the limit as b goes to infinity here is going to be g of infinity. Well, that's going to be our horizontal asymptote of 5 minus g of 2, and g of 2 is simply 9. So we're going to get 1/2 times 5 minus 9, which I believe is just going to end up giving us an answer of -2. So pay close attention to the limit notation. That's going to be a really big part of earning all those points on an improper integral. And then also pay attention to the idea of connecting horizontal asymptotes to limits at infinity. And then don't forget, when we say a function has a horizontal asymptote in general, that doesn't mean that x has to approach infinity. X can also approach negative infinity, right? So horizontal asymptotes can occur in either direction. But in this special case, we restricted our graph to greater than or equal to 0. So there's no way to get to negative infinity. So we want to share those couple problems with you. A whole bunch of extra problems on here you can try. I hope that you'll try them out. Don't forget the answers will be on there later tonight. And then this is another example on here. So as always, we have a couple of surprises. So before Tony reads the tweets out, after the tweets, a couple of surprises today. And then we will talk about what's coming up tomorrow, the rest of this week, and then moving on. So Tony, Tweets with Tony is back in session. What do we have today?
For our AP Teachers Rock, we want to give a special shout out to Miss Hecht from Chaparral High School for being a great Calc BC teacher. Her method of always covering our homework assignments in depth of really helping understand the topics on another level. So thank you, Miss Hecht, and all the students from Chaparral High School. AP Students Rock, we've got a special shout out for an individual that I know. So proud of the BC Calc students from the 7, that would be Glendale Union School District, just outside of Phoenix, Arizona. So proud of them who show class and dignity by showing up virtually and in person each day to be better at calculus. You'll be the one solving problems tomorrow. I'm proud of you. And we want to extend a special thank you to an amazing rock star teacher, Kim Thomas, who sent that particular tweet to us. So thank you to everyone. And keep those tweets coming.
Yes, absolutely. Keep the tweets coming. We love them. Don't forget our AP Calc exam information. Tony and I have been gearing these lessons around this. We haven't been spending much time recently talking about it, but make sure you take note of the date and the time for your time zone and then what's going on. And we'll spend more time talking about that in the coming weeks as we get closer to the exam. And then tomorrow, fundamental theorem of calculus. This is a pretty important lesson, Tony. Would you even almost call it fundamental?
It is a fundamental lesson, no doubt.
All right. I think we might have just lost our remaining viewers after that joke, but it'll be a really, really important topic that we'll see throughout the exam. And we've done a lot of that already in these last couple lessons, so just be an extension of that and more formalizing of that. Don't forget, we have some technology help if you need it. So always keep in mind that website cb.org.tech/tech. If you or anybody you know might have some device or internet access issues and need to get help, please do that sooner rather than later. That way you can make sure that you have exactly what you need to take the test when it's time. And so thanks for watching. Surprise number 1. Here we go. We have our dog or cat of the day. So our dog had lots of dog photos and pictures and things sent to me, so I thought we would share some of them. So this is our dog of the day. This is Maggie Grace. She's an Australian Shepherd, and because I am leading this, I get to have some bias in my selection process. So I actually chose for the first one of my own students, Emily's dog. It's a brand new puppy, so I had to give her airtime on there as well. And we'll see how jealous Buddy and Loopy become. But if you have a favorite dog or cat or any pet, really, feel free to tweet to us, right? At PassWaterB or at AP Calc Teacher. Spell notice the spelling of both of those. If you tweet us, maybe your dog or cat or pet or fish or whatever you have, lion, tiger, we'll make it on the air for our dog or cat of the day. So with that said, I think our final surprise today is we might get Grover back. I heard to show us some of his dance moves. Is that right, Tony?
Hello, everybody!
Grover, are you ready to jam out as we exit here today?
Yes, I am. Thank you so much for being such a good teacher today, Brian. I think I start to understand calculus.
So what you got, Grover?
Yes, AP Calc. Welcome to AP Calc. Yes, AP Calc.
Calculus. Data polynomials. Infinite series. Differential equation. Calculus. Data polynomials. Infinite series.
And another warm welcome to everyone here for AP Calculus BC Live. And as you can see, we are continuing our week-long series connecting AB BC with today's specific topic, fundamental theorem of calculus. And as with all of our videos, we encourage you to download the associated materials. They can be found in the description below the video as a direct link to our Dropbox. And you've probably noticed here lately we have a sort of a mixture of our problems. We have these quick checks at the beginning that are sort of standalone, isolated problems that focus on the topic of the day. And then we segue into a pair, or in some cases, some days we have maybe 3 or 4 free response questions where we can then sort of weave or integrate, no pun intended there, the topic of the day into future AB topics and into topics, in this case, into the BC realm. And boy, do we have a couple of really great FRQs today. So very long FRQs. We almost ran out of letters of the alphabet to break those FRQs into parts. So a lot of great content that you're going to see in that regard. We also have great news to share. We'll probably share that at the end of the show, but we will be doing a few more episodes at the very end of the month of April, and we'll talk about those where we're going to be able to help the kids get a little bit more acclimated to this new form of this AP exam this year. And so stick around for that. And we also have our dogs of the day as well. My name is Tony Record. I am joined by my esteemed colleague and good friend, Brian Basswater. And Brian, I tell you, I just think this keeps getting better and better. I keep thinking I'm in some dream here. I'm so fortunate to have this opportunity to work with students, to work with you. So it's just been great.
Yeah, it's been amazing. And Tony, I always mess this up because I always look the wrong way. I need to go back and watch these on YouTube because you're always looking the right way, and I think I was looking the wrong way trying to figure out where you are. And so I think Tony's like the tech savvy guy. You always talk about Tony being the tech master. Brian is the guy that knows what's going on half the time. But I think I'm looking at you right now, right? Can you see me?
I think so.
Okay. Yeah, I mean, we're definitely pinching ourselves. So Tony and I, we've done a lot of work on the College Board, but I remember, when I first started teaching 10, 15 years ago, I loved College Board. I wanted to be a part of it. I loved the AP curriculum. I would see names out there of AP calculus teachers that I wanted to emulate, that I admired, and there's still people out there. I remember when I first started teaching, you were teaching before I was. I knew who you were and wanted to be like you and some other teachers. And I remember this was a story I'm going to tell us real quick, but I've been reminiscing a little bit because a lot of our students here are seniors, and so they're missing out on a lot of those great senior traditions. At my school, we would have some senior pranks, right? And they were always good natured and nothing bad, and I won't go into details about what they were, but there was one that wasn't so much a senior prank initially, but it became one at my expense. And so when I first started teaching calculus, I enjoyed the College Board. I don't know how it worked, but we were doing one of these FRQs, right? And the students have seen a lot of the FRQs, these response problems I'm writing each day. And sometimes you get these FRQs that are really, really cool. cool, right? These college board problems are really unique, and wow, what a neat question. I think teachers more often say, what a neat question. Tony, when you tell your kids, oh, this is a really cool question, does that there mean they're gonna hate this question? Like, if we love it, they're like, that's not a good sign, right? It's gonna be really hard or different, kind of confusing at first for them. But the college board comes with these really cool questions. And one year there was a problem that was beautiful. That was amazing. It was my first year teaching Calc BC, and it was so amazing. In fact, in the moment we did it, I was like, guys, we have to stand up and get college board a round of applause. So we stood up in class, we gave a standing ovation. I'm not exaggerating. And I was so moved by the problem, I actually wrote college board a letter, just thanking them, like how beautiful the problem was. I wrote a letter, and I think I went online and looked at college board's address. I don't know who, but it's to the college board, dear Santa Claus. Sent it to them. Not pretty ignorant about how the whole thing works. Well, about 2 weeks, 3 weeks later, I got a letter back sent to me. It was sent to my school. It was sent to me from the college board, and it said, thank you for your letter. We appreciated it. Normally we don't get complaints about our problems. It's so nice to have someone appreciate and our effort and appreciate what we did. And we really enjoyed that. Thank you so much. And I was so proud of the letter. I actually had it framed. I framed not just the letter, but I framed the envelope that came with it. I made a frame for it. Not exaggerating. I hung it up in my classroom. And for like the next, probably 3 or 4 months of school, I would brag about that letter and that thing all the time. It became this running joke in class that every day I would brag about my letter from college board, how that made me important, how cool I was. And the last week of school, again, I was bragging about it. And my student said, Mr. Passwater, we wrote that letter. And I was like, no, you didn't write that letter. You guys are playing a prank on me. You're trying to make me think you didn't, And they had their laptop with them. They turned the laptop around and they showed me whatever the program, the Photoshop they had done. And they wrote the letter. And I'm gonna tell you, I couldn't tell if I was impressed or devastated more because they went and found a letterhead that looked like college board, and found all the college board names and put it on them in the margins with their titles. And another teacher signed it, and a real, like the person who was a college board employee in case I looked it up. And the teacher kind of faked the signature. And on the envelope, they even printed a fake postmark stamp on it. They put a stamp on it that had a fake postmark as if it had gone through the mail. And they stuck it in my school mailbox. I would think it came directly mailed to my school. It was a pretty elaborate prank. And I was kind of half devastated, but I kept it hanging up, And so I still have the letter, still have it. But it kind of made me miss the senior pranks. It kind of made me miss some of the things. Like I definitely feel for our seniors who are out there today that are kind of missing some of that. But we're looking forward to a great lesson today. I'm looking forward to jumping right into it and doing some really cool problems involving the fundamental theorem today.
All right, well, let's go ahead and get us started. And as you already have seen, the fundamental theorem is our big focus of the day. And if you want to think, what does the fundamental theorem of calculus really say? Well, it says a lot of things, but I guess the first thing that we want our students to really grasp from that is it's associated with the area under the curve. So as you can see in the picture, we just decided to call this curve f prime of x. It could be anything, f of x, g of x. We're going to do a lot of manipulations with area under prime today. And so if we were to integrate that f prime from a to b, that's going to depict that area under the curve. And we call that the fundamental theorem of calculus. But there's just so many different ways that we can find that area. It doesn't always have to be some integration technique, some manipulative type of procedure that's used in an analytic environment. It can certainly be used in a geometric environment, and conceptual environment. And those are the things that we're going to try to expose you to today. So that's what we want you to think about. Fundamental theorem of calculus associated with finding the area under the curve. And so we've got today's big idea, fundamental theorem, but we also have these subtopics that we're going to weave in, like area approximations, finding these exact areas, connecting things, and accumulation. And so our topic on the left side kind of begets our approach on the right side. Area approximations, why not? Riemann sums, trapezoid approximation. The way that we've been talking about these for the past couple of weeks. Now, finding exact areas, that's where we're going to spend a lot of our time today because there are really a lot of different ways to do that. 3 that we're going to focus on, whether it's geometric procedures, whether it's using straight up the FTC, or possibly properties of it. And then we can connect integrals and derivatives with the fundamental theorem, and of course the idea of accumulation, which sometimes we kind of associate that with this fundamental theorem of calculus part 2, right? And we're going to focus on a few of those problems a little bit. We call that modified fundamental theorem. So as we said before, we're going to go ahead and dive into some quick checks, which are some isolated problems here that have maybe 1, maybe 2 parts that will feature these subtopics. And our first subtopic is Riemann sums and area approximations. So from this particular problem, it reads that we're going to let f be a function that is twice differentiable for all real numbers. The table above gives selected values for f prime in the closed interval 2 to 12. Our job is to use a right Riemann sum with the 4 subintervals indicated by the table, by the data in the table, to approximate the definite interval of f prime of x 2 to 12. Show the word that leads to your answer, which is always work. So if we decide to label what we're doing, this is great communication, by the way. It's something that certainly wouldn't be necessary, but if a student were to identify what they're about to do, we're about to approximate this definite interval, that would be great. We would certainly prefer that the student put an approximate symbol after that because we are using a Riemann sum approximation. So that's one thing that you want to consider. So there are times that we could look the other way, and if they put an equal sign there, it's not such an egregious mistake that we would penalize the student, but you certainly would at least instill this into your students. And students, you want to also know that you are doing an approximation. Now, the right side of this symbol is what the most important piece is. So what we have to do is know that we're talking about 4 subintervals here. And as you can see from the table, the widths of these subintervals vary quite a bit. They're just kind of all over the place. In fact, there are 4 different values, 2, 4, 1, 3. So with a Riemann sum approximation, we are using the idea of the rectangular shape. And because it is a right Riemann sum, it seems as if the values of the f prime row that are going to be very important will be these guys. So now we just assemble this in the correct manner. So our first rectangle would have a width of 2 and a height that we could define as f prime of 4. Right? And we'll talk about various ways that you can enter this problem here in a moment. And then we would add to that our next rectangle, which would have a width of 4 and a height that is defined by f prime of 8. And we continue this process with our third rectangle, a width of 1, a height of f prime of 9. And then finally our last rectangle with this width of 3 as indicated by the table and a height of f prime of 12. Right? Now at this point, we would have to identify what those values are from the table. We have to extract information from the table. You can't really leave your answer in terms of an f of something or f prime of something, yet they can be defined by the table. So f prime of 4 we can see is equal to 1, and f prime of 8 is this negative 2, and we just continue this process for f prime of 9 and f prime of 12. Now the thing that I wanted to talk about here is you could earn points on the AP exam on any given year, not just 2020, but any given year by having written either of those 2 statements. That would be your first point for usage of the Riemann sum. The key is that you have to show a sum of products. As you can see, I have sums written throughout this, and I have these products throughout. We must make sure that that is written on our paper, whether it's done via function notation or whether it's done via extracting values. That would be acceptable. And as far as this last line is concerned, that would be enough to earn your full credit because it is a numeric value. It can be simplified. I'm not going to go through the specifics of this, but I believe it's going to be free. You can check that out on your own later. But that would be the most simplified answer. But keep in mind, you need to make sure that you present the sum of products. Oftentimes, a student could make one little mistake throughout this. Let's say that one of these products may have been misinterpreted, and you might still be able to earn a point for the Riemann sum approximation. We sort of get you that little wiggle room. But I think our goal is to try to be as accurate as possible. Let's make each one of those products accurate. All right, so that takes care of our quick check 1 for Riemann sums. Let's move on to check number 2, which is going to focus on the idea of using geometric areas. And I'll do part A on this one. So it says we've got g prime, which is the function given above on this closed interval negative 2 to 16. And as you can see, it consists of 4 line segments and that semicircle. So part A asks us to evaluate the definite interval from negative 2 to 5 of g prime of x. So one of the things that it's easy to do, and I've done this many times when I've worked on documents that use the idea of the fundamental theorem problems that I haven't seen before. And we have this propensity to take the integral of this g prime of v and say, oh, it's g of x. And I won't argue with that. But okay, so you've got a g of x. What are you going to do with it? You can't evaluate g of 5 and see any kind of crystal clear answer from the picture. So we have to really understand the environment that we're working in terms of finding this area. And because we have a graph of g prime, what better way to actually evaluate this integral than to use the idea of geometric areas? And fortunately, when you have line segments, when you have semicircles, you've got some good clean geometry in your hands. And that's what we're doing here. We're just essentially finding the area from negative 2, which would be all of this triangle here, and this, weird shape here. Well, that's not such a weird shape, I guess, because it does stop right here at the 5. Boy, if we were going to go farther into past that 5, we would be in for some really interesting situations, which guess what your homework is going to be. When you take a look at B later on, you're going to have to consider that unusual shape. So in this case, we just basically have an area that's in red and an area that's in green, sort of Christmas here, that we're going to have to go ahead and add. So if we find that the area that's in red, we see that that's a nice well-behaved triangle that has an area of 1/2 base, the base would be 5, times the height, which is 3. And then the green area we have to think of being below the x-axis, so we're going to have to use a negative for that. And we can see that that's got a base of 2 and a height of 2, and so we have 1/2 2 times 2. And that numeric answer would be perfectly acceptable in this particular case. If we do choose to simplify, it's going to be 15 halves minus 2, which I believe would be 15 halves minus 4 halves, or 11 halves, 5 and a half, 5.5. Okay, we definitely encourage you to take a look at B to kind of capture that nuance of this very interesting shape that's going on there. All right, pushing ahead, as you can see, if you've got the document in front of you, there are a lot of problems. So we're just going to kind of focus on the ones that we think set up some of the parts of our free response questions that we're going to do today. And I'm going to switch over here, quick check 3, part B, where now the topic is the fundamental theorem of calculus. Is it part 1? Is it part 2? Textbooks will kind of interchange those ideas. So as a teacher, don't worry about what your particular book has. Just make sure that you teach both parts. The normal, what we say, fundamental theorem at the beginning here, where we integrate from A to B, and then you've got that other facet that kind of ties into accumulation. It uses the idea of a function defined as an interval, and we're going to see some of those in a little bit. So for part B, we have this chart. The function g is continuous, has derivatives of all orders for all real values x, selected values of g, its first and second derivatives, and capital G, the antiderivative of g, are given in the table above. Our job, part B, is evaluate this integral little g of x from the lower boundary of 6 to the upper boundary of -1. Now we have a couple of things to consider here. First of all, we don't have that luxury of just being able to find geometric area because there's no graph. So we're going to have to rely on knowledge of this antiderivative of lowercase g. Now, fortunately, we were told that that is going to be uppercase g. So that's good news. Now, I know what some of you might be thinking, looking at those boundaries, and you're thinking, wait a minute, those boundaries, they're kind of all messed up, right? The lower boundary 6 is greater than the upper boundary -1. That's normally not the case. They should be switched around. But we're going to talk about how to deal with that later when it becomes important to deal with it. But right now, because we're not using signed areas under a curve, we can leave the boundaries like that. There's nothing wrong with integrating this lowercase g, calling it a capital G, and then just saying, all right, we're going to evaluate the boundaries in that order. So that just means you get capital G of -1, subtract capital G of 6, and then just read those values right from the chart. So that would give you capital G of -1 is +1, capital G of 6 is -2, and so the result of that would be a +1. Okay, now if you switch the boundaries and throughout that negative, it would work. But we're going to talk about that idea in a little bit. All right, I'm going to move on to quick check 3, part D at this stage, I believe. And we have a slightly different stem. The idea is still FEC, part 1, part 2, which is it. And we have the function f twice differentiable with horizontal tangents at x equals -3, -1, 2, and 6. A portion of the graph f is given above on the interval -3 to 6, and it is known that f prime of 0 is equal to 3. So for our part D here that we're going to do, we're now looking at the properties of integrals. We're going to see these come back up in the context of the other things that we're doing as well. So when we get to our free response problems, we're going to see more examples of this. I want to look at another quick idea, which is the second or maybe the first fundamental theorem, depending on which order your book teaches them in, which basically says if we integrate a function from any constant, right, a is going to be a constant, and u is going to be some function of x, meaning u is a variable, essentially, or expression with a variable. So sometimes the books will write it as f of x or something like that. I probably shouldn't call it f of x because we already have an f of x. It's probably maybe I'll call it g of x. It's just some function of x that has a variable there. It doesn't have to be x. It could be x squared. It could be sine of x, right? It could be the natural log of x. It's just something that has a variable in it. And so if we integrate a function f from a number to an expression with terms of x, that right there can be represented by some other function. There's some antiderivative of x that would give us that answer. And so the big connection I think in calculus is we can connect derivatives to integrals, right? We know they're inverses. We know that they are inverse functions of each other, but that means we can differentiate both sides of these. And so if I have capital F of x and I take its derivative, we can use the fundamental theorem. It says that's just going to be f, this original function of whatever that expression was, times u prime. You have to multiply by the u prime by the chain rule, right? So whatever expression you're plugging in to your expression here, you got to multiply by the derivative of that part right there, which is u prime. Hopefully in your class you saw this broke down. I'm not going to go into the proof or why this works, but it's pretty intuitive based off of the fundamental theorem that if we integrate a function, we can just take our result and take the derivative of that result. So seeing it in practice is kind of the best way to see how this works and the simplicity of it. So quick tip number 5 says we've got this table of values of f, and then we have this function g. We're going to do part A. This function g is going to be defined as x squared minus the integral from 1 to 3x of f of t, right? And so part A says let's find g prime. So we have an equation. Anytime you have an equation, I don't care kind of how weird it looks, you can differentiate both sides. I think it's important that we realize differentiating is just kind of like any other function, right? If you have an equation in algebra 1, 2x minus 5 equals 10, you could add 5 to both sides, or you could add to both sides of an equation. You could divide on both sides of an equation. You could square root on both sides of an equation, right? It's something, you know, get to a real answer. We could differentiate on both sides of an equation the same way that we could add, subtract, multiply, divide. As long as we do it to both sides of the equation, we're going to get an equivalent or another true statement, as long as we're in our domain. So if I want to find g prime, let's just treat this as an equation and differentiate both sides. So g of x's derivative is going to be g prime. We've taken that derivative. On the other side, we're now going to take this thing's derivative. Well, x squared is easy, right? This is going to be 2x, no big deal. And then minus. Now I have to take this thing's derivative. How do you take the derivative of a definite interval, right? How does that work? Well, that's exactly what this fundamental theorem tells us how to do it, right? It says if you want to differentiate this, we just take the expression, right? And we can plug that right in for everyone. And so here, the derivative of the integral, those two ideas are inverses, so like the derivative and the integral kind of cancel out, right? They kind of almost undo each other. So we're going to be left with f of 3x in this case. I plug it in. Then I have to multiply by the derivative of what we plugged in. Right? Remember, we have to multiply by the chain rule, which is by u prime. And so since we plugged in a 3x, we're going to multiply our answer by 3. I think one common mistake that students do is they forget the chain rule, they forget that multiply. Or what they'll do is they'll look inside of the parentheses here on their answer and think they have to multiply by the derivative of the parentheses. That's not what we're doing, right? We've got to make sure that what you're multiplying by is the derivative of the upper bound here, or the lower bound, wherever the variable will be. It just so happens that when I plugged it in, we still got a 3x in the parentheses, so it kind of worked out the same, but really make sure that you're multiplying by the derivative of the upper limit, which would be 3 in this case. And so now that we have this, we can figure out what g prime of 2 is. And g prime of 2 just means plug in 2 for all of our values. So 2 times 2 is going to be 4 minus f. If I plug in 2 here, it becomes f of 6 times 3. And all of a sudden, this table of values up here starts to make more sense because if I want to find f of 6, I can look right at the table at the minus sign on the subtraction side. F of 6 is going to be 0. That worked out nice, didn't it? 4 times 0 times 3 is going to be 4. So we get 4 for that one. We're not going to do part B, but I want to illustrate what I mean by why we're multiplying by the derivative of the limit and not what's in parentheses. Because on this example, when it says find h prime of x, well, first of all, our limits are expressions in the bottom limit, right? So one thing we could do is realize, remember, we can use our properties of integrals we just talked about, and we can flip those limits. We can write that as cosine of t squared minus 1 with a negative sign in front. So now I'm going to plug that limit in. We're going to have a negative in front of our answer. And when I go to plug it in, it's going to be cosine. And if I plug in the natural log of x for the variable here, it's going to become the natural log of x, the whole thing squared, right? Minus 1. That's what we would get if we plug that in. And we know we have to multiply by the chain rule, right? That u prime. Well, that's what I mean by saying don't look here. We're not multiplying by the derivative of this. We're always multiplying by the derivative of what that boundary was, right? So you're multiplying by the natural log of x's derivative. And natural log of x becomes 1 over x, right? So that's what I mean by saying make sure you look at this piece and not what's in the parentheses. Because sometimes what your upper boundary is and what you get in your result are the same thing. So we're going to, with another quick check on, there's a lot of extra good problems that you can look at. I want to push past quick check number 6, this accumulation model, because we're going to see it on one of the FRQs here in a second. So we'll leave these for you to try. And then I want to jump over back to Tony so we can get at least a glimpse of a couple of free response problems that will take these ideas, put them into practice with other ideas, as well as connecting us to some other AB topics and some BC topics so you can get a better feel for how these things might all appear together on a free response problem this year. Certainly, I think what I will do here, I'm going to skip ahead, and after all, this is AP Calculus BC Live. So why don't we jump into a BC question? So if you're kind of flipping through, following along with the document, I'm going to go to BC1, part N as in Newton. And I know you might be looking through that problem, or at least looking at the side and saying part N. Well, that's not where it ends. It has a few more parts. It goes up to part P. But you know, that's not a surprise. It's called the fundamental theorem of calculus for a reason. It's very fundamental. It permeates through so much of calculus. By the time you get to say this, around the second semester of an AB course, the more calculus that you would take after that, you're not going to shake this idea of the fundamental theorem. It's going to pop up in almost everything that you do. So in this true BC question, we have this graph of f prime of x, and the function f is continuous and differentiable for all x. And a portion of the graph of f prime, the derivative of f is shown above, and the interval for which we see it is from -3 to 6. We know that f2 is -3. That might come into play in some problems. We are asked to evaluate the definite interval from 1 to 3 of sine of x times f prime of x. Now, I may have given this away by saying it was a true BC topic, so you have to think about what kind of integration technique you want to employ. But seeing as how you see the product of two functions, one of which is what we call transcendental, that just kind of means weird, right? Those are the weird functions, trig, inverse trig, ELX, natural law. It's very likely that the only choice that you might have to integrate is to use integration by parts. But you have this elusive f prime of x that's going to be problematic, and that's going to play a very big role in deciding what you want to let your u equal and what you want to let your dv equal. So if you kind of sit back a little bit and think about this, f prime of x, how elusive is that, especially on the interval 1 to 3? If we were to look at this graph at 1 and 3, we should notice that the f prime is just nothing more than that line segment. So you are not going to have such an elusive f prime after all. You are going to be able to find the equation of that, and I think that's it's going to be a necessity in order to solve this problem. So a couple of different ways you can do that. You can just use the simple idea of a couple of points, 3, 2, 1, -2, and we can find the slope fairly easily. Let's say if I take the difference of the y's, I would have 4 over the difference of the x's, which is 2. So our slope is of course 2. Pick one of the 2 points. I'll choose this guy here, and we can use our point slope formula very nicely. And let's go ahead and solve this completely for the y, and we would have 2x minus 4. And really what this y is, it is the function f prime of x equation. Well, at least for a little bit, right? It's valid on the interval 1 to 3 at least. And so that's what we're going to use. We're going to place that 2x minus 4 in for that f prime of x. And now once we've done that, we can make our decision about what our u and dv are going to be. Again, students, teachers set this up a variety of different ways. The table method will still work here as long as you're clever and you want to use the algebraic piece for the u. I know there's lots of mnemonics out there like Lie8 and I8 and so forth that can help you dictate what you want your u to be. But just make sure that you choose the algebraic piece here, because our goal would be ultimately to have this disappear, right, into nothing, right? Take as many derivatives as you need to cause that becomes 0. Now for the dv, be very careful here because we have to integrate going upwards to get our v, and the antiderivative of sine is a negative cosine. And now we just assemble our integration result, u times v. And notice what I'm doing here. I'm going to write my u times v. Maybe I'll put my negative sign out to the front, and then I'll subtract the integration of v times du. Well, in this case, I see that I'm going to have a 2 times negative cosine. So I'll tell you what, I'm going to go ahead and change that to a plus and just pop my 2 out front and kind of simplify it on the fly. Now you'll notice that, oh my goodness, blasphemous, I'm not putting in any of my integrate or my boundaries of integration. Well, that's okay. I'm going to erase this equal sign so that I don't run the risk of trying to assume that I'm linking this back to this, because those would not be equivalent to each other. But I'm just going to sort of work this off to the side as an indefinite interval. And then once I'm finished with that, I'm more than welcome. I'm certainly able to reintroduce those boundaries, and then I essentially reset the problem. I know there are a lot of teachers out there that are, no, we don't want to do that. We don't want to do that. I have found, trust me, I teach a lot of students. We have 300 students at my school taking calculus, and I find that so many of them really get lost trying to put those boundaries into an expression that has been integrated and then into an expression that has yet to be integrated. And so I find that they have more success by just working it out without the boundaries. But I re-emphasize over and over again, make sure that you plug them back in. One of the best ways to do that is to circle them in the original problem so that your attention is drawn to them. So to finish this up, we can then see that this guy's not going anywhere. We're just going to let him kind of stay where he is, and then we're going to integrate the 2 cosine, which is 2 sine of x. Now we can just go ahead and reintroduce those boundaries of integration. That's called our restart. And then when we plug our 3 and our 1 back in, I don't think we get something that's necessarily pretty per se, but that's okay. It's going to be written in terms of cosines and sines, but it would look something like this. Just want to be really careful with the usage of your parentheses here, because I need to subtract, and now I'm going to plug in my 1. 2 minus 4 is -2. And I know this looks pretty awful, right? There's a lot that can be done with it as far as ruling out some double negatives and whatnot, but I'm just going to leave it like that and let you clean it up. But it's not going to get much better. We don't know the cosine of 3, the sine of 1, etc., etc. So there's a nice little BC problem that kind of connects this idea of FTC. Ryan, what do you got here with BC2?
Sure, thanks, Tony. So we're going to fast forward to BC2, and I hope you download these files because there's like 16 parts to BC1. Tony just got through one of them because of our timing today, but there were 15 other parts that give you a really good collection of problems that will take you through a whole bunch of AB topics, plus some more integration things that we talked about at the beginning of the lesson, plus more BC ideas, kind of like the one that Tony just did just now. So BC2 also has many parts, maybe like 6 or 7, so it's a lot less. But I want to highlight one or two really quickly before we finish up, because we haven't talked about this much. But part A on BC2 talks about this average value of a function f, right? This idea of how do you find the average value of something. That's an important idea. We know they've taken that out of the AB exam this year. It's only an AB topic. They've taken it out as part of that unit 8 that will be tested, but it will be on the BC exam potentially, so we're keeping it. We haven't mentioned it yet, so we want to make sure we at least one problem today that introduces this idea. So you might remember the average value of a function is given by this formula that I put here in the box, right? The average value of f over interval is going to be 1 over b minus a times the integral from a to b of f of x, right? So you have to be careful that when you see the word average, sometimes we're asking for average value, which is this. Sometimes we're asking for average rate of change or average rate, which is very different, right? That would be the slope of a secant line of the graph. And so in this case, to find the average value, we're going to integrate f. We don't have an equation for f. That's why it says approximate it using a trapezoidal sum, right? So we're going to tie this back in the very beginning. Tony did a really good example of a Riemann sum. You can also be asked to use trapezoids. So to refresh your memory, theorem of trapezoid is 1/2 h times base 1 plus base 2. We're not going to finish this problem out, but I want to get it set up. So I want to point out where common mistakes would be on the exam. So whenever you want to find the average value, it's really helpful to write that formula out first, because what students do is they see trapezoidal sum and they just start going right into trapezoidal sums, and they don't write out what they're doing first. So they either forget the average part in front, or at the end of the problem they realize, oh shoot, I should have found the average value. I have to divide my answer by something, and they end up just dividing by something, and they have these equal signs throughout the problem saying these things are all equal to each other, and they divide by something at the end, and they still use an equal sign, and now they have that linkage error where they have this approximation and they say it equals the same thing but divided by 4. So we want to be careful how you do notation. So setting up the problem is always helpful before you start jumping in, plugging in numbers and doing it. So I would recommend let's just find the average value over the interval from 0 to 4, because that's just going to be 1 over 4, right? b minus a, 4 minus 0 is 4, times the interval from 0 to 4 of f of x dx. If I want to find the average value, I have to come up with this answer right here, 1/4 times the interval. So then I realize, well, I can't integrate f, right? I don't have big F in the table, so I can't use the fundamental theorem like we might want to. However, that's why it says to approximate it using a trapezoidal sum, because we can approximate the integral, right? Remember, when you do a Riemann sum or a trapezoidal sum, what you're approximating is just the definite integral part. That's the piece that you're approximating. So the trapezoid will take care of the part in red, but then we have to make sure we have that 1/4 as well. So this average value is going to be approximately equal. Like we mentioned, we're approximating it. Don't forget we have that 1/4 in front, right? That's the part that students forget, and they end up just dividing their answer by 4. And depending on how you use equal signs, that can be a little bit dangerous of saying a false statement, even though your answer is the right number. And so we have a 1/4 in front, and then we want to approximate the interval using trapezoids. So remember, our trapezoidal formula is going to be 1/2 the height of the trapezoids times base 1 and base 2. And I mentioned the last example, I'm a big picture guy. I like to draw pictures to help me understand. So whenever I want to do something like a Riemann or trapezoid, if we're trying to integrate f by approximating, I draw that generic curve. It's got a picture of f. I'm trying to make it match the table. I'm trying to match the numbers and the heights. I draw the same curve every time. I label f, and I can label the x values along the bottom. We have 0, 1, 2, 4. You'll notice they're not evenly spaced. There's not proper. I know that the scale is off. And then I label the heights of each one. So according to our table, the heights would be 6, 2, negative 1, 0. And I label those next to those vertical lines. And I do that, I realize, okay, it doesn't make any sense. This would be a height of 0, right? This is obviously a height of 0 would be on the x-axis. This is a negative 1 that would be below. But we're not trying to make the picture the correct representation. I'm only drawing this so I don't make any mistakes when I pull my numbers into my Riemann sum or into my, my trapezoidal approximation. So we can see we have 3 regions automatically. That's why it says 3 subintervals. And then for each one of those, we're just going to use our area of a trapezoid. And every trapezoid has this 1/2 in front, so I can go ahead and put the 1/2 out in front. I don't have to write it each time. What I could do is just put 1/2 and then do my h times base 1 plus base 2. And so if this is my trapezoids here. Remember, this piece right here is our height. So from 0 to 1, the height is just 1. And these vertical pieces are going to be your 2 bases. And so when I have the picture there, it's really easy to make sure I don't mess up the numbers or pick the wrong numbers. And so for the first base, the height is just going to be 1. It's this piece right here. And our 2 bases are those parallel sides, which are vertical in this case, which would be 6 plus 2. That's going to be our first trapezoid. And then our second trapezoid is this little region right here. This one also has a height of 1 from 1 to 2. So we're going to have a 1 there. And then our 2 bases are going to be 2 and negative 1. And then finally, our last trapezoid is this little piece right here, which is going to be a height of 2 from 2 to 4. And then our 2 bases are going to be negative 1 plus 0. And I put my big parenthesis around that, and then my big bracket around that. Now I have my whole answer. Of course, we don't have to reduce or simplify because we have a numerical answer. But the key is going to be, don't forget that 1/2. And if you do forget it, don't just divide your answer by 1/4. I mean, not 1/2. Don't just divide by 4. You might want to make sure you don't have any equal sign linkage errors. Tony, in the last example, did a really nice job of making sure that if we're going to do some side work, don't use the equal signs. Do it and then bring it back when you're done. So equal signs are going to be a big deal on the exam. If you say something's equal, we're going to hold you accountable to that. So that was a nice little average value problem that we haven't seen before. I would encourage you to go through these problems because toward the end of question 2, we have a really kind of cool connection to some series problems, right? That unit 10, those series tests that we did, geometric and P series, there's a couple of really nice problems in there, which is why this table has these functions A and B. You might be like, why is there an A and a B in there? Well, we're going to tie these values back into some series ideas. And so you're going to see a good example of a P series problem and a nice tie into some geometric series. You'll also see on both BC1 and BC2 some reminders on doing arc length, reminders on Euler's method, some good Taylor polynomials, all kinds of different things that BC topics. So try those because that's going to give you an idea of how all these things might be intertwined on this year's exam. The real exam, each question, it's not going to be as long as these two, right? This is much longer than the real exam would be. So don't think, oh, this should be a 25-minute problem. It might take much longer than that, but it's giving you all kinds of possibilities of what might be about question for this year's test. So with that said, try those out. This is really good practice for the exam. I hope that you'll enjoy those. And then our friend Ted, as always, will have the solutions posted on Dropbox tonight. And then if you're a teacher, the AP Calculus Facebook group, he posts those around midday once he gets the keys done for that day. So teachers have access to them a little bit earlier than the students would. And so as always, we're going to end our session with some tweets with Tony, followed by some good news announcement Tony's going to share out in our dog of the day.
All right, so we want to keep these tweets coming in. They're starting to get a little bit thin. We're kind of to scrape and find some of these, so we want to encourage you to use the hashtag AP Teachers Rock. And for the teacher side, we're going to give a shout out to my BC teacher, Ms. Hansberry from Little Rock Central High School. She worked so hard to prepare us for the AP exam and teach us wonderful calculus. So a shout out to that wonderful teacher from the great state of Arkansas. And as far as our AP Students Rock, we're really want to try to get more of these in. We know that there are fewer teachers out there that are watching, so it's a little bit more of a challenge for you guys to call out your students, but we certainly encourage them because we're starting to run a little low on these. So for our AP Students Rock, I want to give a shout out to all my AP Calculus BC students. They were all studying and working together to prepare for the examinations despite the challenges. And I know who sent this. It's a wonderful teacher by the name of Mr. Casimir Uchebu from Lakeview Tech, just outside of Kenosha, Wisconsin. I had the privilege of working with Casimir in a training just not too long ago. As always, if you're having trouble, we want you to make sure that you reach out to the College Board at cv.org/tech. And as far as what's ahead, we have a couple of more connecting AP to BC with particle motion and area and volume, and we're going to move into our problem types next week. We'll go into a little bit more detail about the final week, where Brian and I are going to have a wonderful opportunity to get you guys really ready for this year's AP exam by walking you through and having you try a few time questions under a little bit more testing conditions. So I think the only thing left, we're going to recognize a couple of our little doggies, right? The dog of the day, that's Kona and Cody. And how appropriate for Kona and Cody to make an appearance from Galesville, Maryland, because those are the two wonderful dogs that belong to Mr. Ted Gott. He is the third wheel in this wonderful AP Calculus BC machine, and we appreciate Ted, and we want to definitely recognize Kona and Cody. So with that, Brian, great show. I can't wait to get back on with you tomorrow, and we're going to have Anthony G take us out. We want you to stay safe, stay healthy, and keep learning, everybody.
See you guys.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
You want to handle the table, Tony?
I'll let you do that.
I'm going to have you do it.
Okay, I'll do it.
So I will write right now. So after we do our introductions, the intros, when I get on the spot, you'll take over from there. I'm going to play some music.
Calculus. Taylor polynomials. Infinite series. Differential equation. Calculus. Taylor polynomials. Infinite series. Differential equation.
Good morning to everybody. We are so glad that you're joining us today as we continue our week of connecting Calculus AB to BC, where each day we're taking one topic from AB, doing a couple of quick checks, refreshing how we can work those problems, and then looking at how we might connect that one topic to other topics throughout the course of Calc AB and those BC unique topics all in one to get you prepared for the 2020 AP Calculus BC exam. So we are so glad that you are here with us today. We've got an exciting show. I'm going to start calling these shows, I guess, and not this lessons. An exciting show talking about particle motion and making all kinds of neat connections. I feel really excited about the problems that we have today to share with you. So as always, you can find our materials in our Dropbox, and they are hyperlinked underneath the video. You'll see there all the materials we're doing today, tons of extra practice problems as well as solution keys loaded up there. So make sure you take a look at those and follow along with us if you can. I am Brian Passwater, teacher at Speedway High School, joined by my who I thought was my really good friend, Tony Record, but I'm starting, Tony, to question this a little bit. Yesterday I shared kind of an embarrassing story about a letter that I thought I received from the College Board when I was a young AP teacher, and how excited I framed it. I was so excited that my student will prank on me. It wasn't actually from the College Board. And I thought today I'd share another quick embarrassing note because I do enough of them that I can share that pretty much every day of my life. A couple days ago, maybe Monday, we were live on the air, you and I, right, as always. And I did a whole session. And after my wife and I went for a quick walk around the neighborhood, and because these are early morning, this is 9 a.m. Eastern, you and I get pretty early. We meet beforehand and kind of hash out some things and things like that. And my wife's still in bed, like, so I try to be quiet, keep the lights off, and get dressed in the dark, and I come up here, and my eyes are kind of tired and crusty still. When I wake up in the morning, I went the whole session, went through a walk with my wife afterwards, and in the afternoon, and she noticed in our walk that my shirt I was wearing was literally inside out. She said, "Do your shirt's inside out?" was like, oh, I noticed that. And it dawned on me. I did an entire lesson on here on Monday. I think it was Monday. With my shirt completely inside out. And you're my wingman, Tony. You're supposed to catch these things in our live Zoom. What happened there?
I just thought it was like this new fashion statement. I thought you were really trying to show off your drip.
Oh,
That's what I thought it was about.
Okay, yes. So yes, I think the use would say that I am showing off my drip, right? So I definitely am. So that's my embarrassing moment for the week. But other than that, hopefully we can save the embarrassment the rest of the show, and I'll wait till tomorrow to do something more embarrassing. But I'm excited today. We've got some particle motion, and then you're gonna walk us through a really quick sort of formula sheet about what the kids need to know. And then we're gonna jump right into today. We got so many problems we want to get to, so we want to get through as many as we can in this next 45 minutes.
All right, so yeah, we've got this opening page of your document shows you sort of your one-stop shop to all things particle motion. But I gotta be careful when I say all things particle motion. We really are only talking about particle motion as it relates to the rectangular coordinate line. There's so many connections that particle motion has with parametric, and that typically has been the often go-to particle motion question on the BC exams in the past. But since we're not going to be dealing with parametric equations on this particular year's exam, you can narrow your focus to the rectangular world, and that's what this table pretty much talks about. So we're going to call this the particle motion reference information, and a lot of this is likely information that you've already seen in your course, but it's likely that it was taught maybe very early in the year. You know, you of course being BC students, maybe some of you are taking BC as a second year Calc course, and at which point a lot of this was probably taught to you last year. For those of you that take your BC course all in one year, your AV material and your BC material together, this was still probably taught very early on. So you know that x of t is your position, and you take the derivative of position to get velocity, and of course you take the second derivative of position or the first derivative of velocity to get acceleration. Those are your basic foundation, right? But we also have to remember these various things about your direction of motion, and it's really just a matter of knowing what the sign of the velocity is. If velocity is positive, we know that that's a situation where the particle moves to the right. If velocity is negative, we know that's a situation where the particle moves left. Particles won't move any other way on this year's AP exam. We don't have to worry about things moving up and down, falling from the sky. There's a separate AP exam that talks about that. That's called AP physics. Speeding up and slowing down, very big idea when it comes to particle motion. And your big focus is going to be basically talking about the signs of the velocity and acceleration. If those two signs are, excuse me, what I call in tandem with each other, that basically means that if the velocity is a sign that's say moving this direction and the acceleration is the same, it's like there's a force that's holding on to that particular particle that's just going to tend to make it go faster. But on the other hand, if the velocity is say going in this direction and the acceleration is another force that pulls it from the other side, then obviously that's going to slow down that particular particle. So you're going to look at the comparison of the signs to determine if the particle speeds up or slows down. Position at time c, very important concept that deals with, yes, the fundamental theorem of calculus, which we talked about yesterday. So we're going to use this idea to find the position at any time c is just going to be a matter of taking the position at the beginning of that time interval, a in this case, and then adding that accumulated change of position. And that's what the interval of v of t from a to c is going to be here. Now, if we're talking total distance traveled, that's a little different when we need to invoke the whole absolute value idea, because we don't want this velocity to be kind of positive and negative and going all over the place back and forth, because that's not going to give us a very good depiction of total distance travel. So we take all of those chunks of time that maybe the velocity was negative, that's the particle moving left, and we sort of trick it into thinking that the particle was moving right that whole time, and thus we can accumulate a total distance traveled. Okay, particles change direction when the velocity changes signs, right? We kind of talked about that before. And then of course the speed, sometimes we call that the magnitude of the velocity if we're dealing with the vector world. But when we're talking about just parametrics, we're okay just to call that the absolute value of that particular velocity. So of course, if we integrate that, we'll get total distance travel. So let's go ahead and take a look at our first quick check here. And I'm just going to do a couple of parts. We're just going to kind of do bits and pieces of our quick checks because we've got some wonderful free response questions coming up. I think that you're going to really like that. Our VC2 is a doozy. It's got a part 1, a part 2, and a part 3 with separate subparts and a lot of things going on in the problem, from a particle moving to popcorn being sold at halftime of a football game to a young male human growing through their first 13 years of life and beyond. So lots of neat things in store. So for quick check 1, for the time interval 0 to 12, we have a particle that moves along the x-axis. The velocity in meters per second of the particle is modeled by the function v of t, which is shown in that figure above, and it consists of our 4 line segments in that quarter circle that happens to be centered at 10, -3. The position of the particle x of t at time t equals 3 is going to be -2. So our first question is, for the time interval 0 to 12, when is the particle moving left? And we have to give a reason for our answer. So this is where that communication piece comes into play. So as we look at our reference chart, and you're welcome to kind of flip that back and forth, if you're able to even take it off to the side, maybe don't even staple your packet together, but have that off to the side, and you can always refer to it as you're working through these problems. You may have noticed that that particle is going to move to the left when the velocity is negative. So we just simply look at our graph. It is a graph of velocity, and we can see it's from this time interval 0 to 3 that graph lies below the x-axis. And then again, we see that happening from the interval 9 to 12. All right. So what we could do, if you want to write this really kind of nicely, you can say the particle moves left, and it's probably nice to use a good preposition here. We're going to talk about a time interval, so I would avoid the word at and maybe use the word on, use the word over, something that connotates an interval. So we could say on the interval 0 to 3. And notice I don't really want to include the endpoints here, because at the endpoints we know that the velocity would actually be on that t-axis, which makes it a 0 velocity, and it's a situation where we're neither moving left nor right. And then again, we see from 9 to 12. And so there's our answer, but we need to connect that to a reason. And the reason would just simply be because v of t is less than 0 on those intervals. You don't even have to say that your v is equal to 0 at those endpoints, because it's implied in this particular instance because of the intermediate value there. So that would take care of your part A. Part B is a wonderful part that I would like to leave it to you to kind of look at a little bit, finding the position of the particle at time 12. But if you use your reference sheet, you can see a very nice way to get into that particular question. And you're always going to be able to check these with the keys that we have posted here, in about 24 hours or so. But I would like to talk about C, because we've just begun to address this issue with this concept here just recently. And I have, Brian and I always have certain predictions about the AP exam. Of course, we don't know exactly what you're going to see, but I'd like to talk a little bit about what our feelings are with this particular concept. So we're trying to find 1/9 times the integration of v of t from 0 to 9. And then we want to use correct units and interpret the meaning of this interval within the context of the problem. So the first thing that we want to do is go ahead and evaluate this definite interval. So I see that 1/9 is nothing more than just a constant that I'll bring down. And then I look at this integration of v, and I have to scratch my head and think, well, I can't really truly integrate v, because that's going to give me a position. And I really don't have a lot of information about position in this problem. In fact, I really only have one piece of information, and that's the position at time 3. So what we need to do is think about another way to evaluate this definite interval, tying into what we talked about yesterday with fundamental theorem. We're just going to find the area under the curve v of t, between the curve and the t-axis here. So as we see, this area from 0 to 9 consists of 2 parts. And I'll just kind of shade in the first part. And this sort of magenta colored part is kind of interesting, because we see that it lies below the t-axis. And then as I move more forward, I move into this blue shaded region, and that's going to be, of course, above the t-axis. So we just have to remember that we treat any area that's below the axis as negative and above the x-axis or t-axis as positive. So moving into this problem, we have this area of this magenta colored triangle that will be negative, and we have the formula 1/2 times the base times the height, and the base is 3, the height is 2 in this case. And we want to double check and make sure that our scale is all uniform, which is going to be very important in a problem that we see later on. And then we would add, and you can break this figure apart a variety of ways, but I would trust by now we're starting to feel pretty comfortable with the formula for the area of a trapezoid. It's kind of a big deal in calculus, right? So we can use trapezoid formula. So 1/2 times the sum of the bases, and it looks like we have a base here at the bottom that's a length of 6, a base at the top that's got a length of 3, and then the height of this trapezoid is going to be 2. All right. So when we put all of this together, we end up with 1/9 times the quantity. Then we have a -3 here, and we have basically a 9 at that point. And then we could go ahead and simplify this. It's going to be 6/9 or 2/3. And again, we say this often. Your degree of simplification is really up to you. You had us at this first step. This would be acceptable because it is a numerical value that would be equivalent to this 2/3. But now we have to use correct units, and we have to interpret the meaning of this interval in the context of the problem. And what we want to train all of our students, Brian and I, in our own classrooms, and we'd like to do the same as units, likely that your teachers have already done this for us, But anytime that you see an integration expression with that coefficient of this form, in other words, you see that the difference between the boundaries is what resides in that denominator underneath a 1. So in other words, you see this sort of 1 over b minus a times the integral of an integral from an a to a b of, well, I'm just going to say some function, right? Some function of some variable. This is always just going to be interpreted as the average value of that function. Insert the name of the function, whatever it depicts in the context of the problem. In this case, that function is velocity. So when we go ahead and interpret this, we could just say this is the average. Now, if you want to say the average value of velocity, it would certainly work. It's probably a little overkill in the words because you could just simply say the average velocity. Now, there's an acronym that you can use called NUT that a lot of teachers use. If you've never seen this before, maybe it's likely you've seen something else similar in your classroom, but we kind of let the N stand for the noun or the number in the problem, U is the units, and T is the time. And those are the three things that you must address whenever you're interpreting the meaning of whether it's a derivative or an integral. So I'm starting the building blocks of the noun part, right? The average velocity, and I know that's 22 thirds, so that sort of takes care of the number. And we need to get a little bit more context. How about we say the average velocity of the particle? That kind of gives us a little bit more clarity. Okay, well, what is that average velocity? We just computed it to be 2 thirds. Okay, but now we need that unit. And so the unit here, well, if we integrated the velocity, now remember the velocity was measured in meters per second. So I guess if you go up to this particular graph, we know that this was meters and this was seconds. And by the time that we found area, which is what the integration process is, we have meters times second, right? All right, well, we got this meters times second, great for this area, but then all of a sudden we're going to have to take into consideration what we're going to be doing with this one night. Well, wait a minute, that meters times seconds is also going to have to be tempered with the fact that we have this dt. So in essence, what we've just found is meters, right? Whenever we integrate this velocity, that second drops away, right? Because we have meters seconds over seconds. The meters drops away, but then this division by this new element of time is going to invoke that new idea of seconds being in the denominator. So the average velocity of the particle would be 2 thirds meters per second, which is probably not too far-fetched because that's kind of what you would think velocity would be measured anyway. But we're not done yet. And the reason we're not done is because we don't have the t element. And this is usually one of the most common ways that a student wouldn't earn full credit on the interpretation. So what we have to do is know that this is the interpretation of an integral, which means we use an interval to depict what's happening. So we want to use a very good word like on or over. I don't like the word at to interpret the meaning of an interval. And we'll say we could use the word interval. That's fine. It's a little bit more powerful. And we know that we're starting at t equals 0. We're going to t equal 9. And you do want to go ahead and label that time element here, which we know is in seconds. And that would be a really strong argument. That would be a really strong exemplary answer for that interpretation. There are a few things that you could alter to still get full credit, but these are the kinds of things that we like to show our students. We like to show them the most exemplary answer to hold that bar really high. All right, I think we're going to move on to quick check 2, if I'm not mistaken. And I believe Brian is going to take the lead here. Right, perfect. So we're going to go through this one a little bit more quickly than the first one. We want to make sure we have some time to get to these, at least a couple of these FRQs that we have at the end of the lesson today. So looking at quick check number 2, so talking about that example where it was a graphical example, right? So we're always trying to show you different representations, we would call them. So sometimes you might get a graphing problem, you might get a table problem. I think with the way this year's exam is going to be done, there's probably a certainty that we're going to have a lot of graphs and tables on these two FRQs because those are two ways that we can, generally speaking, eliminate the use of technology as an aid to students, right? And so these are good examples that I think might prepare you well for this year's exam. So quick check number 2 says, okay, we have a new particle now. It's moving along the x-axis, kind of similar to what we had before. And the position is x of t, and we're doing it for 6 seconds. And then we have in this table the position x, the velocity, and the acceleration. All three things given to us. Now we don't know what's happening between those values, right? That's one of the big mistakes I think that students make is when you're working with a table. Generally, you don't know what's happening between each one of those points. And sometimes we make assumptions about what's happening, and we can't do that. Students might say, well, here the velocity was 0 and it was 5. So the velocity increased, during this time to 5. We can't say that because it could have gone up and down a whole bunch, right? Because we don't know what's happening between 0 and 1. So there's some things we can figure out from tables. This is where your existence theorems come into play a lot. Intermediate value theorem, mean value theorem, those kind of things work well with tables because they know even with only a little bit of information, we can still make some guarantees. When you see a table problem, I tell my students, it means you're probably going to be doing some approximations. Since you don't have all the information, you don't have a graph or the whole equation, you might be able to approximate some answers, or you might be able to do some existence theorems, guarantee some things like IBT or MBT. In this case, we're going to look at a unique problem that Tony mentioned on the first slide. We haven't seen an example yet. Is the speed of the particle increasing or decreasing at time t equals 4? I think part of the confusion is that when we drive a car, a lot of times we push the gas pedal, right? We say, oh, we're accelerating, and we think the gas pedal is accelerating. And so what happens is we get this misunderstanding that whenever you go faster, you are accelerating, right? You have a positive acceleration, and that's not actually how it works, right? Acceleration is any, or positive acceleration, right? Acceleration in general is any positive change in velocity. So it turns out in your car, your gas pedal is an accelerator, but so is your brake pedal. Every time you brake, you're also accelerating. And your gas pedal doesn't mean you are accelerating positively, and your brake pedal doesn't mean that you're accelerating negatively. It depends on which direction you're moving in the first place, right? And so when somebody says a particle speeding up or slowing down, the big misunderstanding is, oh, that means when you start going faster and faster and faster, it means that you are going, you're speeding up, right? But what we have to be careful for is that when we start talking about speed, it requires us to consider not just the velocity, we have to also consider the acceleration both. We have to take both of those things into consideration. Velocity tells us which way we're moving, and acceleration tells us sort of like which way we're pushing. Are we pushing forward? Are we pushing backwards? And those two things combined will determine whether you're speeding up or slowing down. And so if we look at the time t equals 4, we're looking right here, and we know from the table that our velocity at 4 is -3. So v of 4, our velocity is -3, and a of 4, our acceleration, is going to be just -1. So what's happening here? So the negative velocity, and by the way, our position happens to be at -2. That's pretty much irrelevant, right? We don't really need to know where our position is, but at time 4, we're at -2. Here's my particle. Negative velocity means I'm moving toward the left, right? We have a velocity that's negative, so we're moving toward the left. And then think about what the acceleration is telling us. Acceleration tells us which way am I pushing you, right? Imagine this particle is moving toward the left, and then the acceleration is negative means we're pushing it toward the left, right? Whenever the acceleration is negative, it means you're pushing toward the left direction. So not only is my particle moving left, the acceleration is pushing it in that same direction. Our acceleration is negative, which means it's pushing toward the left. And what's happening? You're moving left, and someone pushes you left. Imagine you're walking somewhere, and someone comes behind you and pushes you in the same direction. It doesn't matter which direction you are going. If someone pushes you in the same direction you're trying to go, you're going to have that jolt, right? And you're going to be speeding up when you do that. And so this is why if something is speeding up, we look at both acceleration and velocity. And since they're both negative, we're actually going to be speeding up. And so we can say in a problem like this that the particle is speeding up at t equals, what was that time? 4. And our reason will just be because v of 4, our velocity, and a of 4, our acceleration at that time, have the same sign. Whenever they have the same sign, it means we're pushing in the same exact direction that we're moving. And they have opposite signs. They're kind of conflicting. You're trying to go one direction, but you're pushing in the opposite direction. When that happens, no matter what, you're going to be slowing down that. Then we're going to mention part B here, and I'm not going to go in depth on it because Tony is going to hopefully get to a nice problem that will address this in a more contextual way. But here we have this integral of the absolute value of v. And so when you're doing a Riemann sum, you got to be careful on your table because our table is velocity, right? Sometimes we get so used to making a Riemann sum, just adding those numbers up, which is what you do if you're integrating velocity. But here we're not integrating v, we're integrating the absolute value of v. So we have to keep that in consideration when we're adding these things up. And then we're also asked us to interpret the meaning of this. Hopefully you can remember when we integrate absolute value of v, you're going to be coming up with a total distance travel question. There's a difference between integrating v
v versus integrating absolute value v. One of them is your displacement, and then this one is going to be our total distance travel. So I'm going to leave that one for you. I want to kind of lay that as groundwork to get ready for what's going to be coming up here in a little bit. And then finally, quick check 2, part C says, when do we know the particle's moving toward the origin? I like this example because it reminds me of the speeding up and slowing down problem. And we see those speeding up and slowing down problems on a lot of previous exams, but we don't see a whole lot of questions like this in recent years. And so I can see this being a nice little twist that college work for one of these tests. And again, it's important because it requires two things, right? Just like speed does. If you're moving toward the origin, if you say, oh, you're moving left or you're moving right, you don't know if you're moving toward the origin or not. It depends on where you are, doesn't it? And so if we're going through this problem, let's take it at these different times. So let's say, what happens at t equals 0, right? I like to always draw pictures. It helps me know what's happening. At time 0, we know the particle's at -1, right? So which means the origin is here, right? Our position is -1, but what's our velocity at that time? It's 0. So we have a particle here, it's not moving at all, right? It's just sitting still. So it's definitely not moving toward the origin. So that one definitely is going to be out. What about at t equals 1, the next particle? Now our position is at 3, according to our table, right? So our origin now is going to be over here because we're on the positive numbers. So our particle's sitting right here at 3. But which direction is it moving? It's got a positive velocity, which means it's moving toward the right. Well, we can easily see from our picture we're moving away from the origin, right? So that one's definitely not going to be it. What about t equals 4? Well, at t equals 4, our position now becomes -2, right? So here's our origin over here. And then which way is it moving? The velocity is negative as well. So which way we're moving? We're moving left. Negative velocity means you're moving left. Ooh, guess what? We're still not moving toward the origin because we're left of the origin and moving toward the left as well. And so I'm hoping, unless I made a mistake, that this last one is going to maybe work out. And so at time equals 6, we are at -4, right? So where we are. So our origin is going to be over here in this case. And which direction are we moving? Well, our velocity is a +2, which means we're moving toward the right. And now all of a sudden, guess what? We are moving toward that origin. But we only figured that out because we considered where the position was and the direction of motion both. So when you see problems that maybe look a little different than what you've seen before, it's a little confusing, draw some pictures, draw some sketches to help you get an idea of what's happening. So this is the only time that we can guarantee it is. Again, it could be happening other times. We don't know what's going on in between those numbers. That's why it's the only time that it's going to be certain. So that's going to be quick tip number 2. And I'm going to leave off the explanation part of it just for time's sake, but that'll be in the answer key. It'll be very similar to how we laid out the explanation of speeding up and slowing down. But Tony's going to walk us through some parts of another FRQ that will connect some particle motion to some other ideas as well. So Tony, what do you got for us here?
Yeah, in fact, I may do maybe more than just walk. I may run you through parts of BC1 here because we've got some really neat things we'd like to get you exposed to at the end. But in BC1, what we got is a graph of velocity. Again, I'm going to paraphrase some of the stem of the problem. And we have these signed areas of this value of 6, that's soon to be -5 and 18, that will lie between this curve and the t-axis, the time axis. And then something kind of funny is happening here. After time 9, right here, we're redefining the velocity equation for this particle that's moving, this v sub p particle. And it's going to be called 45e to the -k times t power. And all we know about k is it's some constant between 0 and 1 inclusively. We also know that the initial position of the particle at time 2 is 7. Now, I'm just going to gloss over 3 really parts, and I may not write a whole lot here, so you might just want to listen and then you kind of fill in some of the packet when you work it on your own later. Part 8 is a pretty simple question. Find all the times t on the interval 0 and 9 at which the particle changes directions. Give a reason for your answer. Well, if you remember to our reference sheet, particles will change directions when they change, when the v of t changes signs, right? We change from going to the left to going to the right or vice versa. So how do you interpret that graphically? Well, you just simply look and see where does this curve cross the t-axis. We don't mean bounce off of the t-axis. We mean physically move from the upper side to the lower side or vice versa. So the answer to A is 2, 5, and you could write that up. And the reason would just simply because v of t changes sign. You don't even have to say that v of t is going to equal 0 at 2, 5 because it's implied by the intermediate value there. Although if you say that, it's a strong argument and it hurts you. Part B asks to write an expression that involves an integral that gives the position x of t and use that expression to find the position of the particle at time t equals 0. But once again, your reference sheet at the beginning of your packet will really walk you through the process of finding any position given the information that's provided in this step. Now, with this particular setup, we're trying to find an expression for x of t. So we'd really like to know, hey, where is this particle located at any time t? In order to be able to figure that out, you're going to have to know where the particle starts. And we only have that piece of information provided at time 2. So we know that x of t is going to start with this x of 2. And then from there, we will accumulate some more positional change. And we do that by using a definite interval, starting at where we begin with our initial time 2. And then we take this up to an unbeknownst time to us that we're going to call t. Okay, well, that's kind of interesting because this is working out to be a function in terms of t. Well, what is it that we integrate? We, of course, integrate the velocity. Now, I don't want to go into a lot of detail about what the heck do we put here, right? What goes into those two spots? Because we can have an all-day discussion about this, and we'll circle around and really accomplish very little. A lot of times teachers say, oh, we must put this dummy variable. We must put some variable there that isn't a t. I would certainly want to stay away from maybe using x. Maybe k would be such a great idea to use. So really, it doesn't matter what you use. In this case, maybe I use s, right? But it's just that. It's a dummy variable because this is going to be a function in terms of t anyway. As soon as we integrate this, aren't these s's going to disappear and this t is going to pop into play? Now, that being said, what if a student or a teacher for that matter used t in these two cases? It's not the end of the world. It's okay. The problem still makes sense. We could go around and around. We could talk about all the order of operations and how that impacts the problem. So I think a lot of times we make too much of a deal out of the use of the dummy variable here, okay? And at that point, you would just go ahead and say, well, if I want to find the position at time 0, then we just replace the t with 0. What's nice about this expression is that you can use it to find the position virtually anywhere now. That's what's great. And when we go into this particular graph, we see, oh, well, if we want to integrate from 2 to 0, well, that's a little backwards, right? So no harm in just switching those boundaries from 0 to 2, kind of treat it a little bit more conventionally. Of course, that brings out a negative sign. And at this point, we could go ahead and probably find that area fairly easily, right? We have that set up to be a 6. Remember that x of 2 was 7, and of course, 7 minus 6 would be 1, and that would be the position of the particle at time 0. And then the very last part of this problem is kind of interesting. It's sort of a teaser. Make sure I get to the right part here, part F. It's sort of a teaser for tomorrow's lesson. Let R be the region bounded by the graphs v of pt and the t-axis from 9 to 15. Write but do not evaluate an integral expression that gives the volume of the solid generated when R is rotated. I'm just going to kind of paint the picture here for you. Basically, we can extend this axis out to 15, and we could say that this graph 45e to the -kt. I don't know what it looks like, but you know what? I really don't care. I do know that it's fairly well behaved and it's not going to dip below a very important line that I'm going to be using in this problem, and that is the line v of t equal -1. Well, here's that horizontal line. Let's just put it down here. We know that it's going to be below the t-axis, so this will act as our axis of revolution. Okay? And then if we take into consideration this region that we're going to bound, we would have to set up some representative rectangles. And let's go ahead and maybe just really quickly show you that region because it says this graph is bounded by the t-axis. So maybe it looks something like this. I never did real well coloring in between the lines, but that's about as good as I can do there. So what we've got going on here is a decision. A decision must be made about how you would set up this volume. We have disk method and we have washer method as our two primary go-to procedures for finding this rotational volume. And in this particular case, you could set up a couple of representative rectangles. The first one looks something like this. We'll go into a lot more detail with this tomorrow, but I always like these rectangles to be set up so that they start from the axis of revolution. The first one would go to the farthest boundary, which is the curve itself, and we can call that capital R. And then the next one will go to the nearest boundary, which would be the t-axis in this case, and we would call that little r. And then it becomes a matter of finding out what the expression is for capital R, top minus bottom, little r, we can do top minus bottom. Assemble that correctly into our nice volume formula. Don't forget the pi. Everybody likes pi. And boom, we've got a great set of our volume. But like I said, I didn't want to go into a lot of detail with that because that's going to be our teaser going into tomorrow's lesson. And this is going to give Brian a chance to kind of move on to the rabbit hole that we call BC2. Is that right, Brian?
Yes, let's go ahead, Tony, and I'm going to skip over here to BC2. I'm only going to look at a couple of parts, but I want to make sure that we understand at least what the stem is talking about because we're going to be using this multiple ways. So the big idea is this. Particle motion is always a big important idea. We've seen a lot of AP exams where particle motion is one of the entire free response problems is revolved around particle motion. BC a lot of times, parametric idea is a lot of times one of the free response questions. But we were confident there won't be a parametric free response since it's not on this year's exam. We're probably not going to see an entire particle motion question. So we're probably not going to see an entire problem that's, hey, is this particle motion? It might show up as like a part C or a part D in the midst gist of a bigger idea. So that's what we try to do here with BC2. We have 3 parts to it. Each part has like multiple subparts. It's a gift that keeps on giving. So here's what they have in common. All 3 of our cubes use the same table. We have a table of values for a function f given, and then we're given a graph of a function g. And all we know from the stem is that f and g are continuous as long as for all values t greater than or equal to 0. And then we have a couple of values given to us in the table for f, and a portion of the graph of g, meaning that this graph of g will keep on going. And then we also know that when t is positive, the function f is increasing. So f is always increasing for all of them. So we're going to start looking at a little particle motion idea. So we have 2 particles, particle p and q, and then moving along the x-axis. And now we have the idea of 2 particles working together, and they have positions x of p and x of q, and then their velocities are going to be v of p and v of q. And essentially, what we're doing is we're defining this table is going to be the velocity of particle p, and this graph is going to be the velocity of particle q. So these are velocity equations that are given to us. And then we're going to look at a couple of different pieces of this. So part A says find the total distance traveled for particle q. So if you see 2 particles in a problem, you got to first be careful like which one, which graph, or which table are you using, and then also then start breaking down the ideas of what it was. And so this one wants us to find the total distance traveled. And so before I even look at the graph or information, I would always tell my students set up an integral for a problem like that. So total distance traveled is going to be the absolute value of the velocity, right, integrated from the limits of 5 to 10. I was going to set that problem up a lot of times on AP exams. Just that one setup, just applying the formula to your problem and knowing how to set it up is a point. Like, that's the first point in a lot of these problems, is knowing which equation, which expression, which integral idea is going to get to our answer. And then once we have that, then we would start computing that. And the idea here is, again, this is the graph of velocity. So normally, like I was talking about before, we have all these shaded regions here, right? We have one above, and then this little piece below, and then another piece below. And what do? We would take the positive ones, we would subtract the ones underneath because they're below. That doesn't apply when we have absolute values, because if I just said what's the integral of velocity, then we would take a positive minus and a minus. But we're doing the integral of the absolute value, which means if we were to take what this graph looks like, it would actually take these 2 ideas here and it would reflect them with it, because it would be the absolute value, everything's positive. So all the values become positive. So if you're doing total distance traveled and you have a graph, those parts that are underneath the graph, you have to make them positive and instead of subtracting them. So I'm not going to finish out that problem. I want to lay that down and let you try it, and then you can check our key to see if you applied it correctly, or if you're a little bit confused still, you can see our workout solutions and then see what we're talking about by why we're adding those values and not subtracting. But the one I really want to get to is part B and part E, these last 2 parts of BC2, part 1, because this is going to re-hit an idea I mentioned earlier about find the times when the particle is speeding up. And so on the first one, it was kind of scaffolded. I gave you a specific time, and I said, okay, is it speeding up or slowing down at that time? Well, here, I'm not going to give you a time, because you find all the times when the particle is speeding up. So remember, in order for something to be speeding up, it means the acceleration and velocity have the same sign, right? Which means the velocity could be positive and the acceleration could both be positive. Or, right, remember we have 2 options here, or they could both be negative. And a lot of times, this is the part that students forget about, is that they could both be negative. You could be accelerating in reverse. Imagine you put your car in reverse, right? You slam on the gas pedal, you start zooming backwards. You're still speeding up, aren't you? So since you're speeding up, your velocity is negative and your acceleration is negative because you're pushing backwards. You're going to be speeding up. So you can speed up in either direction. So we have to look for both of these ideas. If v is positive and a is positive, and we're given a graph of v, that means the graph is positive, so we're above the x-axis, it's a positive graph, and the acceleration is positive. Now remember, how do you find acceleration? That's the derivative of velocity. On a graph, if you're thinking derivatives, you're thinking slope, right? So we're saying v is positive, the graph is above the x-axis, and it has a positive slope. So where on this graph do we see the graph above the x-axis and have a positive slope? That would be right here. This is the only place where both of those things are positive. So we have the interval of 0 to 2. And then finally, we have this other idea, which is v is less than 0 and a is less than 0. So now we're below the x-axis and a negative slope. And that's going to happen a couple of times. Both of those cases, we're going to see the graph is below the x-axis and the graph has a negative slope, which means a is negative, which is going to happen from 6 to 7 and from 8 to 10. So we're going to have a couple different intervals on that one. Now, I want to highlight part E, and we're not going to spend much time on it. I really want Tony to be able to get to a really cool problem here on the next step. But I really want to challenge you to do a couple of these on your own, because they will make a lot of connections with particle motion to other things in A, B, and BC. And part D is a really cool problem, really nice conceptual problem. I want to start by that, because that's my challenge problem for the day. That might be one of the hardest problems on this entire packet. So try that one out if you really want to challenge yourself. Don't get discouraged if you're struggling. There's other problems that would be more important and more like what you might see on this year's exam. But part E, I think, is certainly valid for this year's exam. And it involves particle motion, the mean value theorem, in a different way that you're probably used to seeing, and Taylor polynomials. So we're telling you not to apply the mean value theorem, but we're telling you the conditions are met on an interval. And then we want to find the second degree Taylor polynomial for the position of particle P. And particle P was this first one, and then approximate the position at time 3. So it's a really cool problem. I don't want to leave that for you to try, but I want to point it out because it does bring back in those Taylor polynomials and gives you a really good glimpse of how particle motion might be connected to a lot of other topics. We can throw in some mean value theorem and some Taylor polynomials all in one problem. And that'll be worked out solution-wise in the Dropbox. So I want to show you that. But then I want to fast forward a little bit to say we probably aren't going to have a stem, a problem that starts out on this year's exam. This is particle motion. It's probably going to be this table and this graph represent kind of a generic idea like we had here, this kind of initial stem. And then later on in the problem, they might introduce particle motion or other ideas as well. So Tony might give us an example of how this stem might apply to a different topic. So Tony, what do you have for us that we can look at that would address something that would be not quite particle motion but the same graph and table?
Well, it follows on the very next page. This is our version of free response question stem recycle. You see the same exact table. You see the same exact graph of g of t. And in fact, the preliminary stem reads the same. The functions f and g are continuous. Selected values of f are in the table. A graph of g is shown. But now if you look at the part 2 language, a completely different context. During the halftime intermission at a college football game, popcorn is made and sold at several concession stands throughout the stadium. For time 0 to 10, the rate the boxes of popcorn can be made can be modeled by m of t, and the rate the boxes of popcorn are sold can be modeled by s of t. And both of those are going to be measured in boxes per minute in this case. M of t is equivalent to f of t, and s of t is the absolute value of g of t. So that's where we can kick back into those 2 pieces of information, that table and that graph, and use it in a completely different context. It's really cool. Brian did a great job of assembling this. It's one of my favorite problems of this set. T is going to be the number of minutes since halftime began. Both m of t and s of t are measured in boxes per minute, as I said. And at time t equals 0, there are 120 boxes of popcorn. So sort of that initial position. Well, it's not particle motion, but it kind of acts as the same thing. And I want to just kind of talk through here for part A. It says find s prime of 1. I want to make sure that this shows up. This is a prime mark. It may not show very well on our slide, but it does show up a little bit better, I think, on the handout. So find s prime of 1, use correct units to interpret the meaning of that in the context of the problem. One of the things that's really important is that we tell students a lot that we have to know what these functions are in the problem. This s of t, might look like just some normal everyday function, but when it turns out that s of t is a rate, right? In fact, you can read through it and it says the rate that boxes of popcorn are sold is s of t. So it does not look like a derivative, but it acts like a derivative, right? Even though if it doesn't have any kind of derivative demarcation to it. Now, if we're going to take s prime, we are looking at the derivative of the derivative in this case. So notationally, we could say, well, s prime of 1, well, I don't really have a lot of information about where I can, take the derivative of just an s in that particular form, but I do know that s is the same as the absolute value of g. So maybe from a notation standpoint, we can think of it like this: the derivative with respect to t of the absolute value of g of t. I got to be careful because there's a little bit of a linkage problem there. I have on the left side a specific derivative point, but on the right side I have a general derivative, so I can maybe clean that up by using some notation that looks like this. Just an option. All right. So now I have to figure out, well, what is the derivative of that absolute value of g at time 1? So I go up to this particular graph. I see at time 1, I do have a point that lies on that graph, but I don't want to call the answer, let's say 40, because that would be the absolute value of g of 1. I want the derivative of the absolute value of g of t evaluated at 1. So I have to look for the slope here, and you've got to be very careful because the scale change could get us into big trouble here. And notice that we have a vertical scale of 10 units and a horizontal scale of 1. So it's pretty clear that we have 10 over 1 as
that particular slope. And that turns out to be that numerical answer. Now, as far as the interpretation is, there's a few different ways that you can do this, but there's some key elements that you have to provide here. So what we could say is s prime of 1 represents, well, the very first thing that we like to tell our students is you have just taken the derivative of a rate. Remember, s of t is a rate. So let's start with that word. Brian and I are very similar in that we teach our students to begin in that fashion, right? So we have this rate. Okay, well, what's this rate doing? Well, we took this derivative. So we have this second connotation of a derivative that has to be embedded into your explanation. Now, you can do that so many different ways. If you use the nut system, maybe we can get into our idea of our noun. So the rate at which popcorn, and I think S stands for the fact that we're selling popcorn, right? The rate at which popcorn is being sold, but I still don't have that other idea of a derivative. So now I could kind of interpret this value 10 as a positive number. So we could maybe really supercharge this question and this explanation and say that that is increasing. I always like to tell my students, if you have a positive result for the derivative, you have an increase. If you have a negative result for the derivative, you have a decrease. So s prime of 1 represents the rate at which popcorn is being sold is increasing, and then we put our value in by 10, and the units would not just be boxes per minute. That would be boxes per minute. It would have to be boxes per minute, right? Because we have this second derivative idea. The rate of change of boxes per minute would be boxes per minute, and then we have to make sure that we address the time element, and that would be at time equal 1 minute. Now, are there other ways to do this? Of course. I want to make sure that you emphasize the fact that if you underline those two words, rate increasing, there's your two derivatives. If you say s prime of 1 represents the rate of popcorn being sold, that will work because you have the word rate in there twice. So you just have to be very careful. That's some of the language, and as long as you got the two derivatives connotated kind of verbally, you're going to be in pretty good shape. Right? I'm going to hand it back to you to see if there's anything that you want to kind of close out with.
Sure, Tony. So I'm going to flip the screen here to my screen, and this is the third tier of the problem. And I'm actually not going to get into this because it wouldn't do it justice to try to do like 1 or 2 minutes. We'd be rushing through it, and you wouldn't get much out of that, and you would lose kind of like the really coolness of the problem. So I think what we're going to do is I'm going to save this problem in its entirety, and then next week is a whole entire week about problem types. So we're going to be looking at just tables one day, how those might appear on the exam, just graphs, and all the different topics. So we're going to take one type of problem, tables, graphs, equations, and then verbal type ideas each day. Think about how all the topics across the course will be asked in those ways. And then Friday we're going to put it all together next week. So I'm going to save this for Friday because it really does give all three representation. We have a table and a graph and an equation, a lot of verbal components going on. So it's really kind of a neat problem. It's pretty rich. So I want to make sure we do the entire thing, or at least most of it on Friday. So I'm going to skip on that for now. So even if you're looking at it, if you do it, you might recognize it again next Friday, but you might consider skipping over part 3 of this step. But it reuses the same table, and it starts off with a logistic problem. And it goes through a lot of examples, a lot of second derivatives, Euler's methods, all kinds of fun activities, Taylor polynomials, all in the problem. So we're going to save that for next time. But we do want to flash forward a little bit, like I mentioned, and talk about what's coming up next week. So we just finished day 22. Can you believe you've been attending these for 22 days? I would love to see if anybody's attended all 22. If you've been at all 22 of these, you have to let Tony and I know. We'll put our Twitter handles up here in a second and then tweet out that you attended all 22 so far. That'd be cool to see who has been here every single day with us. But tomorrow we're going to be connecting area and volume together. Another big AB topic. And this is something interesting because today particle motion and tomorrow area volume. Those are AB ideas, but they're not on this year's AB exam. Now particle motion will be in terms of derivative ideas, but all the integration ideas, total distance, displacement, position, that stuff is not tested on this year's exam for AB. And area volume, that unit 8, that includes rate in, rate out, like the popcorn problem that we did today that Tony mentioned, and the area volume tomorrow. Those are things that are excluded from the AB exam, but 100% they're going to be on potentially the BC exam. And so sometimes we think, oh, we got to just focus on the BC topics. We got to make sure we hit those topics that are AB ideas. So I think there's a good chance we could see a piece of a question like that as well. Tony hinted at it today with that one part. We'll do more of that tomorrow, as well as connecting those across the curriculum. Like I mentioned, next week are going to be these different problem types. This will be a really good example each day of how one FRQ can cover just so many different things in the curriculum. How one table can do, here's one big FRQ. So those will be really good lessons. I hope you'll join us for those lessons as well. As always, if you have any tech issues, the website is there, collegeboard.org/tech. You can pause your screen if you write that down and get a hold of it. But make sure that everybody you know has what they need for the AP exam. And as everybody mentioned, tweet out to us. We had a couple people, Tony, that actually created Twitter accounts just to tweet out either about their students or about their teachers or about their dogs or just about the lessons we've been doing. So tweets with Tony is here. And Tony, what do we have today?
Yes, thank you for those tweets, everybody. We were kind of having a pretty dry well there for a while, and now it's full. So we're going to be able to share a lot of these. So keep them coming. AP Teachers Rock. We want to recognize this particular individual. We would like to give a shout out to our calculus teacher, Mrs. Fox. She is the coolest math teacher ever and always wears different math themed t-shirts. She was also the first math teacher to finally tell us that contrary to popular belief, 0 divided by 0 does not equal 1. Wait a minute, doesn't 0 divided by 0 cancel, Brian? Isn't that equal to 1? Okay, okay, maybe that's an indeterminate form. Okay. And then for AP Students Rock, we're gonna give a little shout out, Mr. Brandon Trainer, Mr. T. Mr. T pities the fools that don't know the chain roll. Luckily, the AP Calc students at Mitchell High are safe. They have continued to grind over the last 5 weeks that we have been out of school to prepare themselves. So proud of my monarchs. So we'd like to give a special shout out to the students at Mitchell High School in Newport News in the great state of Virginia. So keep those tweets coming, and we'll keep airing them and recognize fabulous teachers and fabulous students.
Absolutely. Our dog of the day today, and by the way, or cat, right? I know we got cat lovers out there, right? I might have to show my own cats tomorrow because they're getting mad at me. Dog or cat of the day, right? Today's dog of the day is Derby. Derby is from Megan. She tweeted out Derby. And we have I got lots of messages for dog of the day. So if you are sent to me, don't worry, I haven't lost it. We're going to work those in. Give your dog some love here on YouTube Live. And our Twitter handles are there at PassWaterB and at AP Calc Teacher. Notice the spelling of both of those. Tweet at us, and we will love to hear about your awesome AP teachers, your awesome AP students, or your dog, catfish, whatever of the day. So thank you so much for joining us, Tony. I'm excited for tomorrow. We're going to wrap up a great week, and we're on the down stretch, right?
We sure are, sir. I'm looking forward to it. I'm going to miss it when it's all done, but we still have so many great things to cover, so we want you to stick around. Keep coming back.
Awesome. And Anthony's going to take us out as always.
Stay safe, everybody. Keep going.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.
Calculus, data polynomials, infinite series, differential equation, calculus, data polynomials, infinite series, differential equation.
Welcome back, everybody, to another exciting edition of AP Calculus BC Live here on College Board's YouTube channel, coming to you live every morning, 9 a.m. Eastern, 6 a.m. Pacific time zone, Monday through Friday. Today, Tony and I have a great lesson planned for you, talking about area and volume, and then connecting that to other topics in AB as well as topics in BC. As always, the link underneath the video, you'll see a hyperlink there for our Dropbox. You can download the materials we're doing today with lots of extra practice problems. And then every evening, you're going to find a solution document with step-by-step workout solutions typed up by our friend Hancock that you can take a look at and see whether you're doing the other problems correct, and maybe where some of your misunderstandings and misconceptions are. As always, during the interview sessions, I'm joined by my good friend and fellow calculus teacher from the great state of Indiana, Tony Recker. And then today, Tony, we are going to be talking about area and volume, and it looks like you've got something going on. What is that, Tony?
Oh, sorry. This is my new toy. toy. No kidding, just got this yesterday. The timing couldn't be any better. One of my really good friends, Mike Rates, thank you so much for doing this. He 3D printed this really cool model we just found an STL file, and it kind of mimics the volume that can be found by using representative cross sections. In this case, semicircles. And then we have other inserts like squares that are in red. We have rectangles. So I'm really excited about this. I can't wait to show this to my students in my classroom when we get back.
Well, I think I need some better friends. I don't have any of those, but I did see. I was wondering if you saw my text this morning. I said, hey, make sure you wear our Brentwood gear today. So I noticed that you must have read that. You didn't respond, but good to see that you're participating today.
That's right, baby. Brentwood Spartans representing our good friends outside of Pittsburgh, Pennsylvania today. And I'm glad that wait, Brian, did you wear your shirt?
Yeah, I told you I was going to wear. Oh, crap. Hang on a second. I'll be right back.
Every time. Anyhow, we want to give a special shout out to Katie Phillips, a fabulous teacher from Brentwood, Pennsylvania, and all of her students who are working really hard and getting prepared for the BC Calc exam. So we thought we'd represent them a little bit today. Interesting fact about Katie Phillips, she doesn't mind me saying, Katie Phillips has got a fabulous past and was actually at the World Trade Center during 9/11 when she was working as a broker. And has many great stories that she shares with her students in the area and the community about that particular day in our American history. So
yeah, that's great. And Tony, I gave you a hard time yesterday because I told the story about wearing a shirt inside out during the entire YouTube lesson earlier this week. So I did it on purpose to see whether you're going to actually be my wingman finally and make sure I didn't do it for an entire episode. I appreciate that. But did you remember to get the socks today as well?
Oh, yeah.
Yeah, did you get your socks? I got them right here. I'm not going to put them on right now, but there you go. Those are like the Brentwood / I think like the Harry Potter cloak of invisibility socks. You put them on, looking at your feet there, they kind of disappear half the time. So it's like a half-working cloak of invisibility there. So congratulations to the students at Brentwood for joining us each day. I know that Katie talks so highly of her students, how proud she is, and we're proud of you guys, as well as everybody else who's out there, students and teachers joining us. Tony, I got a tweet yesterday from a student out on the West Coast who gets up every morning at 5:30 a.m. just to join us live. And my wife won't even get up with me at 8:30 in the morning when I do these sessions. So it's incredible the amount of stories. And I made a comment yesterday about how many students have joined us for all 22, now 23 sessions. And there's just been a ton of things that people have talked to us. They've been watching all of these, whether they're live or recorded. So it's just been incredibly humbling and incredibly exciting to see how many students are pairing. So because they're on here for that, I know that they don't want us to delay anymore. They want to jump right into some problems. And so, Tony, I think you're going to be leading us off and giving us a quick overview of area volume and a couple practice problems. And we're going to jump into some really cool FRQs here a little bit.
That is our plan this morning. And if you're able to grab the document, we've got some really interesting graphics that might tell the story a little bit about area volume. Teachers are welcome to implement these graphics into your notes or lessons in the future if you so choose. Students, you've got a wonderful reference that will help you kind of differentiate between the various kinds of volumes that we can find. So our first phase, we'll focus on the area between curves, which is one of your last sort of AB topics before you sort of foyate into some really heavier BC material. And the idea is just that we're shifting from finding the area between a curve and the x-axis to the area between two curves. And so you can see the progression of how that can happen graphically here. That ultimately segues into the formula that we all know and love, right? We just simply integrate a top function minus the bottom function. And that's really our mantra today, taking the top curve minus the bottom curve throughout that interval and integrating. Now, sometimes those curves can get a little wonky, and maybe we're going to do our integration with respect to y. So that mantra top minus bottom will change to right minus left. And the first quick check is one that I'm going to leave for you. Right off the bat, I'm going to put you guys kind of into the fire here. But you're finding this area that's bounded by these graphs that you can see that are written in terms of y. At least that first equation is written in terms of y. And we've gone ahead and sketched this region for you. It's a little bit hard to see, maybe the shaded region would be outlined by this highlighting here, let's say. And you are to find that particular area. And what we have to do is we have to understand our strategy is either going to be with respect to x strategy or with respect to y. And that's all tied into that representative rectangle. And if we try to draw the representative rectangle vertically, well, really some bad things happen. Some really bad things happen because as this rectangle kind of moves through the shaded region, and if you can kind of pretend that it changes its length, it's kind of all over the place. You know, we have the parabola over the parabola, and then we've got the line over the parabola, and then over here we've got the line over the exponential function. So just craziness is happening. However, if we could take the shape, and if instead we decided to make it, if we decide to make this picture that of representing a horizontally drawn representative rectangle, now we have a little bit more consistency, right? You can always see that the right side minus the left side seems to be that exponential function, which I think is colored in red here, minus the parabola, which I think is colored in green, and that kind of tells you that it's dy setup. And a lot of times I'll tell my kids, do the finger thumb test. The finger thumb test, it's all in the finger thumb test. If you can size up the width of the rectangle, if it looks like this, right, like that, that's a delta y, that's a difference of y, so it's a dy setup, as opposed to a vertically drawn rectangle. The finger thumb test shows that that's a ds. So check out that problem. It's actually one of the few problems that you'll actually integrate all the way to fruition and get a numerical answer, because that's not really our focus today, because we don't think that's going to be the focus on the AP exam this particular year. Next, we have our volumes, right? A couple of different ways that we're going to talk about volumes. One is going to be rotational, and then this one is going to be using known cross sections. And the idea of this kind of goes hand in hand with this little STL file that I had to print for me, and that is using or stacking known shapes together to add their particular areas to get an overall volume. And I think it's not too outrageous to think if you were to integrate an area, you get a volume. Well, yeah, an area is measured in square units. If you integrate something that's square, typically does bring something into the picture that's going to be measured in cubic units, and so it all kind of pieces together. And a quick little picture there. Those of you that might live, right, or teach in the Kansas City area, you probably are familiar with that structure, the Kaufman Center for Performing Arts, which is located right across the street from the Kansas City Convention Center. Why is that important, you ask? Well, the Kansas City Convention Center is where all your AP calculus exams are typically graded. Although that won't be the case this year, but in a normal year, calculus and several other subjects are scored there every June, and the structure is just right across the street. I took that picture a few years ago. All right, let's go ahead and do one setup of a volume using a known cross section. And I'm going to jump over here, part D. Now, what we have in this picture is the base of a solid that is the region formed by the graph of y equals square root of x, the x-axis, and the line x equal 4. Now, for the purpose of our video today, to kind of accelerate things, I've gone ahead and sketched those curves for you. It's possible on a normal AP exam year, this type of a question would likely be A, no calculator, B, more likely multiple choice. Well, we don't have those kinds of questions this year, so you're not likely to see a problem exactly like this, but we wanted to give you this quick check to kind of get you in the frame of mind the problems that you're going to see in a little bit. So what we've got is the base of the solid that's bounded by y equal radical x, the x-axis, the line y equal 4, and in part E, the cross sections are going to be perpendicular to the y-axis, and they're going to be rectangles whose given heights are 4 times y. So if we think about drawing that representative rectangle, let's do it in a color that's a little bit different from what I've got already in the picture. You can put that representative rectangle anywhere. You can give it some arbitrary width, really, a thinness here. It's actually going to be infinitesimally thin, and we can see that that's going to be a dy setup, right? Our finger and our thumb test says that that's a delta y or a dy. So now we have to invoke the idea of what is the area of this particular rectangle. Normally, in the world of rectangles, the area is length times width, or we could think of length times height in this case. And I'm going to define the length to be the distance of that particular shape. And then the height is kind of interesting. The height is like the distance of this shape coming straight towards you. We do this little 3D thing here, straight at your face. So when we put those two ideas together, the length is just simply subtracting the right side minus the left side. So in this case, I have 4 on the right side. The equation is just x equal 4. And then the left side is just going to be that equation, y equals square root of x. Well, wait a minute, I can't put the square root of x here if I'm going to integrate with respect to y. So we have to kind of rethink this y equals square root of x and give it another name, right? And that other name could be x equal y squared. Just another way to depict that particular shape. And so that's the version of that equation that I would like in that particular spot. So there's my right minus my left. All of that would be multiplied by that height that we're given. And it's really important in a rectangle problem that some more information is provided about that particular height. And I think we might end up seeing one of those in a larger free response question today. So it looks like I got my formula for area to turn that into volume. All we need to do is integrate, put our little differential there. It's kind of our third dimension in this case. And then we can integrate from, well, it looks like the lower boundary is going to be 0. And then the upper boundary, be careful, real common mistake. It's very easy. We want to put a 4 here because our mind might be thinking x's, but we want want to put 2 there because of the idea of integrating with respect to y the boundaries that belong to y. So that's just one example of a cross section. There are many other shapes that you can utilize. It seems like squares and rectangles lately have been some of the more common ones that you'd see on the AP exam. Next, and finally, the volumes can go into the whole rotational aspect with discs and washers. And I don't want to go into a lot of detail about these pictures, but they're great references for both teachers and students to have. But the disc method is a little bit simpler version, where when you do your rotation, you are basically looking at the ideas of these representative rectangles becoming these very thin discs. Sometimes we can think of that as a cylinder because it's just simply a cylinder with a teeny tiny bit of width. And of course, the volume formula for a cylinder is pi r squared h, right? Any type of cylinder has that as its volume. And all we're going to do now is just find the volume of several of those. So you can see how we have a pi r squared, and this dx is acting as the height. If you kind of tilt your head a little bit to the side, yeah, that's kind of the height of that cylinder. And of course, if we integrate across some boundaries, that's equivalent to adding several things up and getting a final result. And you can see that the washer method has just a slight difference to that in that we have an empty amount of space. So let's say in this particular problem, this is the region that we're going to revolve around the x-axis here, and we have to end up using both a larger representative rectangle that we call capital R and a smaller representative rectangle, little r, that sort of subtracts off that empty space, that empty area, that empty volume that we don't want included. So I'm going to just hit up one of these, and I'm going to pick a good one here. Let's go to part B, I believe. I'm sorry, let's see what I want to do. That's a good question. Let's go to part B of quick check 4. All right, I'm going to jump right to a really good washer method here. All right, the directions are set up to do not evaluate the intervals that would compute this volume in the described situation. So we have the region enclosed by the graph of 3x minus x squared, and the line y equal x. We're going to rotate around y equal -1. Well, I'm going to draw that axis of rotation in here. That's the horizontal line y equal -1. And as we start to set this up, we want to recognize right away that we are going to be dealing with a washer method. And the reason is because we focus in on the shaded region. We can already see that there's a very large gap between that region and the axis that we're going to revolve around. And then we can also realize that since we're revolving around a horizontal axis, our representative rectangles would be drawn so that they begin from that axis of revolution. So my first one would maybe be about this big if I decide to put it right there. Now remember, you can put it anywhere you want, and that would be the capital R. And then our little r would emanate from that same axis of rotation and just go to the near side of that shaded bounded region, and we can call that little r. And then by virtue of the formula for the washer method, we would just take the top minus the bottom to compute capital R, top minus the bottom to compute little r. And it's very important that those would get squared individually. So in this particular instance, we have our 3x minus x squared subtract -1. You can also change that to a +1 if you want. All of this would get squared. So I have my sort of pi r squared getting developed. My r squared is getting developed for that capital R. And then we would subtract away the value of little r, which is x minus -1. We want to make sure all of that gets squared. And this is what we happen to want to integrate with respect to x. And we'll do so with boundaries from 0 to 2 because this is a dx setup. And of course, who doesn't love a little bit of pi, right? The pi's got to be a part of that particular volume. And we would leave it like that, where we would really have a need to simplify. To sum up, I really like this last quick check 5 that I'm going to leave for you to kind of play around with. But this kind of segues into potentially the way that you could see volume on your exam this year. It's a much more of a conceptual setup approach without actual functions and equations that you would be dealing with. And in this particular problem, we have this graph of y equal f of x, also known as x equal f of y, if we want to rethink it there. And we want to consider the graph of this function shown above, where a and b are positive real numbers. We want to match the integral setup on the left with its corresponding axis of revolution on the right side. So for one, quick foyer into this, how could you think about doing part A? Well, if you see that this is a dy setup, the very first thing that you want to realize is that this requires a horizontal representative rectangle. And because you see a minus the f of y, that might give us a little bit of inclination to think that representative rectangle would go right about here and span that particular shaded region. I've got my right minus my left. And because we're integrating from 0 to b, that means that it's certainly this shaded region that's going to be revolved, and got our pi in front like we're supposed to. So we can start to get a feeling for, okay, this is probably going to be revolving around one of those axes that utilizes this idea of this representative rectangle. And I believe in this case, I want to say we're going to be looking at x equal a at that stage. Right? I have a really wonderful assessment that I give to my students that actually focuses on both regions. I have a region 1 and a region 2, which just sort of brings into play many more permutations of how you can set up a particular volume in this case. So there's your quick check to kind of get you guys introduced to this idea. And I think Brian's going to take it away with a really awesome free response question.
Absolutely. And before we jump into this first question, which I'm really excited to look at, because we know that typically in the BC exam, you don't have a free response problem that's area volume like this. Because in BC we have polar areas, and so if there's going to be a big area question, typically it revolves around polar graphs. Hey, revolves around, that's an unintended pun in that case. It really wasn't. I didn't catch it, so I said it. So we don't typically see a big FRQ like this. I would not anticipate that you're going to see only 2 FRQs, a whole entire question. This is all about area volume, because that's a lot of percent of the exam on just one kind of small topic out of 9 tested units this year. So it's probably going to be mixed in with some other ideas that we see on the exam. So we want to give you an example of how that might happen. What I love about these videos, by the way, is Tony and I in real life really are good friends. We've known each other for several years. We really do drive to get a road trip and go rate the exams each summer, going to nerd camp, as my wife calls it, to grade all the AP Calc exams in Kansas City. But we still teach very different. And last year we started this idea where we were doing these live Zoom sessions with our own students. We thought, we need to have our kids hear other voices besides our own all the time. We also want our kids to hear other teachers explain things and share ideas and insights, because they can learn from other teachers. And so we started doing these live sessions last year for our own students, where I would teach half of them, he would teach half, and my kids would hear him teach sometimes, his kids would hear me teach sometimes, and we really liked it. And we were already planning on doing that again this year when we got the call to these videos. So it's a little bit serendipitous, right? We didn't even know that we were invited. It was like, hey, do you want to do it together? They didn't know we even knew each other. They selected us. And so it was very kind of cool because we were doing these things anyway. But we do teach a lot of things the same, and there are some things that we teach a little bit different from each other. And so it's really neat that for you watching these, you might see different approaches. And Tony and I do that on purpose sometimes. So we know sometimes we approach ideas differently, but because we want to give you multiple ways to maybe think about it, because maybe one of them clicks with you and the other one maybe not as much, or the other one clicks. And so it's really cool that we can do that. And so we're going to tackle FRQ, and I might approach these problems similar to what Tony did. And there might be some approaches I do that are a little bit different, right? They're both equally correct, and then hopefully you can find one that really resonates and then feel really good about that method and do that method, right? Tony and I always say, if you're doing things correctly, then don't change what you're doing. Find anything that you understand and stick with that. So we're going to look at one of these problems. This is a graph of a function f. There's a lot going on here, so I want to just pause for a minute and make sure we understand what's happening here in the picture. So the functions f and g are twice differentiable. So we have our functions of f and g. F is this one in blue, and g is this black line right here. They're twice differentiable, and g of x equals x. So it's just the line y equals x. A portion of the graph, so obviously goes beyond this, are given in the figure, and it's known. Here's kind of a random statement. It's known that the average value of f over the interval 0 to c is equal to c. Can I really give you like a random piece of information? Like, why is that there? It probably is going to be there because you're going to need it at some point in the problem, right? So I always like to underline that. Don't worry too much about it right now, but think, okay, that's there in case you might need it, down the line. And it says part A says find the area of the region R in terms of c. So what I love about calculus is literally what it allows us to do is take something very, very, very small, infinitely small. And if we can find sort of an equation or expression that would give us that little tiny piece, then the calculus, the integration, would add up all of those pieces and give us a total, right? It's that little representative rectangle in this case. And so in my classroom, similar to Tony, I have my kids always draw this little representative rectangle before we go. We connect the two graphs together because it tells us a couple of things. When you make a little rectangle, first of all, it tells you what variable you're using, right? The width, the tiny piece of it is the differential. If it's horizontal, it's going to be dx. If our rectangle was the other way, right, it would have been a tiny little dy. But that tells me everything's going to be in terms of x. But also it tells me I can use that to find one tiny piece of what the question wants, and then let the calculus add up all of those potential rectangles. I drew one example, but we know there's rectangles all inside of here. So if I can create one setup and then let the calculus add the rest of them up, we'll be good to go. And so here, find the area of the region R. So looking at this region right here. So we know we're going to find the area of this little representative rectangle. Well, the area of a rectangle is base times height, and the height of a rectangle, remember the height of something is just the top of it minus the bottom, right? So the height of a rectangle is just going to be the top, which is the graph f of x. No matter where we draw the rectangles, it's always going to be intersecting on the top of this graph of f of x minus the bottom, which is this graph here, which is g of x, right? I'm going to call that x, so that's what it equals. This is going to be the height of a rectangle, and then our width, our base is just that little tiny dx, a little rectangle here. But I don't want just one rectangle, right? This will give me the area of a very tiny rectangle. I want all the rectangles that can fit in here, so that's why we're going to integrate this. And I got to tell this thing when to stop adding things up, right? I always think of integration sign as this big like adding machine, and I'm curious for students too. You can tweet at us. I'll give you our Twitter handles at the end. But in my class, I always use a reference. I always got Pac-Man or Ms. Pac-Man, a video game Pac-Man where he eats all those little dots. I always envision like an integration sign of a definite integral as Pac-Man adding up, eating all of these rectangles, these areas to get a big total. But I'm realizing more and more students don't know what Pac-Man is. You know what Pac-Man is? If you know Pac-Man or you know Ms. Pac-Man, you played those games, tweet at me and let me know so I know the youth of America are continuing the traditions of one of the greatest games of all time. So we're going to be adding these things up. We're going to start here on the left at 0, and we're going to go all the way to the endpoint right here, which is the point. We don't know an actual number, do we? So we have a point, I'll call it C. The x value there is C, right? And so what's cool about this is we think, well, how do they ask area of volume, right? Tony gave us some cool setup problems, which they could definitely do on the exam. But how do they actually make you find area and volume where you're not going to be using a calculator or Google or things like that? Well, here's an example of one. Because you have a little more conceptual part to it, right? So we have to integrate this. Well, to integrate this, we're going to use one of our integration properties that says we can split this up into two pieces, right? It's going to be the integral of f of x minus the integral of x. Both of those from 0 to c. Well, I feel more comfortable with the second part. The integral of x, I can do that. This is my integration properties, right? It's this integral of f. How am I going to compute that? I have no idea what f is. I don't even know what c is. How are we going to find the answer? It turns out that's where this little thing comes in, right? The average value of f is equal to c. Well, how would you find the average value of f? To find the average value of a function, which Tony showed us yesterday. The average value of a function f from 0 to c, right? Remember, you integrate the function and then you divide by the span. From 0 to c is a span of c. And in this case, instead of computing that, the problem told us the answer to that is equal to c. So I know the average value is equal to c. And what would happen if I multiply both sides by c? If I multiply both sides by c, we get the integral of f of x from 0 to c is just c squared. That's pretty cool, isn't it? Because now, hey, what are we trying to find right here? This is the integral from 0 to c of f of x. And we actually just realized because of the average value theorem, whoa, we mixed in another topic, right? I've got area, we've got average value all together. Hey, we're connecting these ideas. That's going to be c squared. So I know this is going to be c squared here. And then I have to subtract the integral of x. Well, we can do that. The integral of x is just going to be x squared over 2 from what? 0 to c. And then we can evaluate that. We still have our c squared from the beginning, right? And then we're going to evaluate the top limit is going to be c squared over 2. And if I plug in 0 is going to be 0. So here's what we get right here. On an AP exam, you can leave it like that. If you plug in values, c is a numerical value. It says in terms of c, meaning c is going to be in your answer. So you can leave it like that. If you wanted to reduce it, it's just going to end up being c squared over 2. So it ends up being a half of c squared. So kind of neat problem that incorporates area, average value in a way that you're going to make you still compute an area without an equation that you can just type into a TI calculator or something like that. So we're going to jump ahead a little bit. And if you're following along with the notes, part B is another cross-section problem. It's really cool. It involves integration by parts. So it's going to incorporate that BC integration idea. So I'm going to challenge you to do that, but because of time, I'm going to leave that one for you because Tony already gave us a really nice example of a cross-section. We're going to see another one here in a minute. We have another FRQ that Tony's going to show us a really cool cross-section approach. So I'm going to leave that for him because what I want to tackle is part G of this problem. So part G of this problem is another rotation problem. So just to give us one follow-up from what Tony shared in the beginning, the picture was amazing, really clear explanation, but I want to give us one more reinforcement of that in case that was a refresher for you. Had seen it for a while, and maybe you learned it, and maybe you didn't quite understand it when you learned it. But Tony shared with us when we're doing rotation problems, the formula, right, for volumes by rotations is just basically pi times the integral of big R squared minus little r squared. And then now that Tony showed us kind of where those numbers come from, we realized, okay, now that I understand what's happening, all we have to really do on these problems, these rotation problems, is figure out what is big R and what is little r. If we can figure out big R and little r, I'm not going to even color code it, then we can immediately just plug them into our formula and we're good to go. So this problem says, okay, we're going to write but not evaluate an expression that gives the volume when R is rotated around the line y equals -2. So I know it's down here somewhere, right? This is going to be my axis y equals -2. And we're spinning this thing around here. I don't have to know what it looks like. And a lot of teachers out there will draw the picture of what this looks like. And that's usually because they can draw, right? If you saw me way back when in one of the early lessons, I draw stick figures. It's not going to look very effective here, so I don't draw the 3D, but you can a lot of good simulations online. You can see what's happening. But here's what I do. I tell my students, like always draw that representative rectangle, right? So it looks a little bit different than Tony's approach, but same idea. But we use that rectangle. That's what we're starting with, right? The tiny rectangle. And I got to find big R and little r. Well, we know that when I have my students do at least, they say once you have your rectangle in the graph, no matter what, this never changes with rotation problems. Take the top of your rectangle and then just connect it to whatever line you're revolving around, right? And make a little connector there. And then take the bottom of your rectangle, right? So you take the top of it to your axis and the bottom to your axis. Before you do anything else, you do that. One of those distances is going to be big R always, and one of them is going to be little r. This is how you can tell. The bigger one is big R, right? And the shorter one is little r. So I went and color coded them. So this little one in red automatically becomes little r, and this big one in blue becomes big R. So if I can just figure out what that distance is, I'm going to have my answer ready to go. So here's where we're going to get our pi symbol. We're still integrating in terms of x, and my limits are still going to be 0 to c. Now big R is from here, the top of the rectangle, all the way down to the axis. Well, how do you figure out how tall something is? It doesn't matter what you're doing. The height of something is always the top of it minus the bottom. So the top of this little region here is this graph right here. So the top of the rectangle is always going to be f. And so big R is going to be the top graph, which is f, minus the bottom of it, which is our line, which is going to be -2. Obviously, you can make that a +2, but I'm going to write it as a minus and negative so you see where it came from. And then we need to square that because that's our big R, right? Our big R is just the top minus the bottom. And then we can go straight to the little r now. Well, little r is just this distance right here. Well, the top of the space is right here. Well, what is this? This is the line, right? This is our line g of x equals x. So we could call this g of x. We could also call it x since it's an equation. Minus, well, the bottom of it is the same axis, isn't it? It's minus -2 squared again. So I make this -2 squared. And then we have our dx on the end, and that's our setup. So it's a nice kind of easy way to set these problems up. Very similar approaches. On the surface, how Tony and I do it might look a lot different, but it's the exact same thing. And so it just looks a little different on the front side of it. But two different approaches we can take that. Let's take a look at a couple of more quick problems where we throw back to Tony here in a couple minutes for this last FRQ problem. This one is part C. We're kind of jumping around a little bit, right? Part C says, okay, we're going to introduce a new function. Here's your AP exam tip of the day. With only 2 FRQs, we're probably going to have this happen on the exam, or maybe we start the problem off with a function in a graph like this, and then part C or part D introduces a new idea to connect it. So you might see all kinds of different letters and equations that happen throughout your exam. Just roll with it, right? You see what it does, always see what happens. So this new function h, not the picture, but it's going to be 2x squared minus the integral from 0 to 2x of f. At least f is back in there. Find h prime of c over 2 and h double prime of c over 2. Well, we can find h prime. Think about all the topics we're covering, by the way. Think about how this is covering so many things from A, B, and B, C, because to find h prime, we have to take this thing's derivative, right? And that's the second fundamental theorem of calculus. I know it wants h prime of c over 2, but we got to find h prime of x first. So I take both sides derivative. 2x squared just becomes 4x minus. Now we're taking this thing's derivative. There's that second or first fundamental theorem of calculus, which says we plug the variable into our expression, it becomes f of 2x, and then multiply that by the derivative of what we plugged in, which is just that. It also wants me to find h double prime, so I'm going to go ahead while I have this here and go ahead and take the second derivative. So the next derivative, well, 4x now becomes what, 4, and then f's derivative is just f prime, right? Now we have a chain rule problem as well. So we have f prime of 2x. I already have the 2 there, but I have to do chain rule of this derivative, which is going to be times another 2. So really it's going to be 4 minus 4 f prime of 2x, and the first one's going to be 4x minus 2 f of 2x. So now we can find the values that they want. It wants me to find h prime of c over 2, right? Tony and I last night were calling the problem of c's, and he wanted to dub it the pass water report card because I was notorious for getting many c's in high school, but I didn't let him do that. He was always a good student. He always likes to rub that in every can. He's got better grades, smarter, better at life than I am, but I'm just doing the best I can over here. So h prime of c over 2 is going to be 4 times c over 2, which is going to be 2c minus 2 times f. If I plug in c over 2 into here, it becomes c, doesn't it? So it becomes 2c minus 2 f of c. Well, how are we going to find f of c? F of c is a point on the graph of f right here. Well, how are we going to know that? Well, it happens to be the same point on the graph of g, isn't it? And g of x equals x. So f of c is going to be the same point as g of c, which is just going to be c. So we're going to get here 2c minus 2c, which is 0. h prime is going to be 0. And then the last part here, h double prime of c over 2 quickly is going to give me 4 minus 4 times f prime of c. Well, this point stops. How am I going to find f prime of c? Well, if f is twice differentiable, that means the derivative has to be the same from the left as from the right. So even though I don't know how this graph is going, I know there's no sharp turn. So the derivative right here is going to be whatever it was as it leads up to that. We don't know what that is. So we don't know what f is, right? We can't actually find the derivative, but clearly it's f is decreasing right there. It's going downward. So that means the derivative has to be negative. So this is going to end up being 4 minus 4 times some negative value, right? Something that's negative, which actually is going to turn into a positive, isn't it? That's going to be a positive value. So our second derivative is going to be a positive value, right? We don't know exactly what it is. So this last part says, is there a minimum, maximum, or neither? But what will happen if your derivative is 0 and your second derivative is positive? Well, it means your graph is a critical point, but you're going to be concave up right there, right? So our second derivative test says if you're critical point and you're concave up, that means it's going to be a relative minimum. And we can say by the second derivative test on that one. Now I want to set up the last part here that we're going to take a look at just really, really quickly. We're going to on part E, not part E, sorry, I'm skipping it. Sorry, to part F. Says find the second degree Maclaurin polynomial. At least want to get us on the right track for this problem so we can see how we're doing it. It says again, a new idea, right? Let's roll with it. Find the second degree Maclaurin polynomial for h, not for h, but for h. Think about our structure. How would you find? Don't get confused by the other information, the 2 cosine, all that kind of stuff. How would you find a Maclaurin polynomial? Well, it's second degree, so we know our degree is 2. Because it's Maclaurin, we know it's centered at 0, and we're creating it for h, right? And so we know that our second degree Maclaurin polynomial, let's just call it p sub 2 in this case, a polynomial at second degree, is going to be always the function at the center plus h prime at the center times x plus h double prime at the center times x squared over 2. Now in the previous problem we just did, remember how we found h prime and then h double prime? So in this case we can just plug in 0 into that problem, right? For the x values to find our derivatives. When we set up our little template here, remember our job to build this, to build the polynomials, we have to calculate all of those f prime, the coefficients, the derivatives. We have to find all these things. And so we can find h prime and h double prime by using those initial values that we have. And then h of 0, well, you can plug 0 in here. It's going to be 0, right? H of 0, we have an equation. 0 minus the integral from 0 to 0. Well, that's just going to be 0. So that one worked out pretty nice. That just becomes 0. But to find h prime and h double prime, we would go back to that equation we had. And the reason why this part here is there is because we're going to need for that equation the slope of this graph right here at 0. And we're not sure what's happening necessarily because it looks like it might be flat, but we don't know for sure. But because it's twice differentiable, the slope at that point is just going to be the slope of this graph. So we can take the derivative and find the slope at 0. So I'm going to leave that for you to try it. But I wanted to bring the idea back to show you how we started with area, we threw in chain rule, second fundamental theorem of calculus. You're going to see some integration by parts, one of the ones that we skipped. You're going to see arc length on this problem, stuff for you. You've got Taylor polynomials. We even have tangent lines in this problem. So all kinds of topics all connected together to see how you can handle those things. So it's going to be really good, I think, practice. So make sure you go back and finish this problem and finish the problems that Tony doesn't get to. And we have one more FRQ that Tony makes really pretty cool at the end that we're not going to touch, but you'll be able to try. So Tony, you want to walk us through parts of BC number 2? Is that what it is?
Yeah, I think I'm going to set up a couple of parts and then maybe work through one entirely. I do want to spend 30 seconds and kind of tack on to Brian's story about our past and academics and so forth. But this is a story Brian will never share with you. But to kind of put in perspective, the type of mind that Brian has. One of us, when they were taking their SAT back when they were a senior in high school, got lost. They couldn't quite remember where the site was and ended up getting there a little bit late. Now, nowadays, that's really a bad thing. You probably wouldn't be able to sit for the test, but things were a little bit looser long ago. And they wrote, that person was able to kind of talk Proctor into letting them start a little bit late. And then that same person forgot their calculator. So they had to take the whole math part of the SAT without the calculator. And ultimately, that same person got a perfect 800. That person was not me. So that kind of puts things in a little bit of perspective, my friend Brian. Take a look at BC2 here. We've got a problem that talks about a cellular relay tower that has a height of 96 feet. The horizontal cross sections of the tower at height h feet form circles with diameters d of h measured in feet. And the function d is differentiable and it decreases as h increases. Selected values for d of h are given in the table. I got ahead and drew a picture because this can be a little bit tough to interpret sometimes. And for those of you teachers that have been around for a while, this might have some kind of lingering memories of the infamous funnel problem that we saw a few years ago. But you essentially have this tapered form of a tower. As you can see towards the bottom, we have this 5 feet diameter. When it reaches the top, we're at 2.4 feet. And then probably there's some relay equipment on the top of that, but we're really excluding from the problem. And of course, tower's 96 feet. Well, when you really start to think about the mathematics of this problem, we have to think about that picture, at least the left side of it, as being drawn sort of like this. Right? We got to think of this h as being the axis that's horizontal, and the d of h as being that vertical axis in that case. So it's a little bit deceptive, I think, when you kind of look at the picture and the math we're going to be doing. It's kind of reminiscent, like we said, of that funnel problem. Now, I'm not going to do parts A, B. I just want to discuss these because we have really tried as best we can to throw in as many existence theorem type problems in a lot of the FRQs that we've done. Part A reads, explain why there must be a value for h on the interval 0 to 96 such that the derivative of h is equal to negative 1/3. And we hope that you look at that and you start kind of getting those creative juices going. You know that this attaches to some existence there. Maybe it's the intermediate value theorem, mean value theorem. We have those ideas that are kind of percolating. And because of the fact that this is a derivative that's given, that's sort of your clue to potentially foyer into that mean value idea. Now, what's really important both about part A and I'm going to move on to part B is there a value for h on the interval 0 to 96 such that d of h is 3.3. Now we're not talking about a derivative. Analyzing data pertaining to d of h, and that will invoke an entirely different theorem altogether. We really would like you to look over your notes, look over some of the things that you've done in your class this year, decide which theorem is which. But that all-important piece, one of the things that's going to be required in your explanation is what is it about this d of h that allows you to use those theorems in the first place. And so you're going to have to read through this language a little bit. We see some information about b being differentiable. So what does that mean? D must be also. And hopefully you're thinking the word continuous, and you want to make sure that that's a part of your explanation in both of those problems. So definitely take a look at those. Part C, approximate the rate of change of the radius of the tower with respect to h at h equal 85. Another wonderful problem that at the end, at the conclusion, it might seem a little bit interesting about what your units are. And I just wanted to talk about that for a little bit. But if you are taking this average rate of change, so to speak here, you will have feet over feet. Those won't cancel because we're talking about a change in the diameter as we move up the tower. Okay? Let's move on to part E. This is the one that I wanted to get out there a little bit. Approximate the volume of the tower between h equals 0 and h equals 96 using a midpoint Riemann sum with 3 subintervals as indicated in the table. This idea of 3 subintervals is going to play very nicely with the idea of a midpoint sum because if we were to sort of skip over every other h value, we're going to find out that we reach that 96 in a fashion that's all too relieving for us. We wanted to make sure that we had that particular relationship. And moreover, it's very important that the values for h right here do lie directly between their corresponding h value to its left and to its right. And we can see that that is definitely happening. Okay. So with that in mind, we can go ahead and start to set up this particular volume. And it is an approximation. And we have to think about, okay, we're using this idea of volume, solid revolution. We have this idea of pi times a radius squared times a height, right? That will give us this volume of the cylinder. Now, this radius is the tricky part in this particular problem because each of these measurements along that bottom row are indeed diameters. So to turn each of those into a radius, we're going to have to divide by 2. That's going to be all too important in this particular case. Okay. And then the h, the height, is kind of appropriately the value of h here as we kind of move from the left end to the right end of each of those intervals. So I'm going to go ahead and bring the pi out to the very front, and then I'm going to start thinking about what's my h in r squared. I'm going to go ahead and put the h in first. So my first rectangle my first representative disk that I'm setting up, its height is going to go from 0 to 40 and have thus a height of 40. And then I would multiply that by d of 20 all over 2 squared. So there's your radius squared. Go to the next figure. We again have a distance from 40 to 80, which is another 40. And now we're going to multiply that by the appropriate radius, which in this case would be d of 60 over 2. And we continue one more time with a pretty thin height over here. When we go from 80 to 96, I believe that's 16. And then we would compute our radius as d of 90 all over 2 and squared. And then from this point, you just have to extract the information from the table, and that would give us the following values. D of 20 is 4. So I'm going to take 4 and divide it by 2 and get 2, and then I'll square that in the next step. And then my next term, d of 60, gives me a d of h value of 3. So far, these are working out fairly well. 3 over 2 is not the prettiest thing, but we'll deal with it. And then over here for the d of 90, we have 2.5 over 2, which, oh goodness, that doesn't look like it's going to be all that pretty. But I think once we decide to simplify, if we decide to simplify, things will start to work out pretty nicely here. We have 40 times 4, which is, what is that, 160, I believe? And then we have 9 over 4 here after we square the 3 halves. And of course, the 40 and the 4 will cancel. And I believe that we have 90 out of that. And for this particular guy, 2.5 over 2, oh, if he was having a dream, he would dream of being written as 25 over 20, which is the same as 5 over 4. So that's his dream. And once I square the 5 over 4, I would have basically 25 over 16. And what do you know, those 16s cancel, and we're stuck here with a 25. And I believe if we were to add all those up, and if I know any kind of arithmetic, and I've been known to not at times, right, we could add and we would get, I believe, 275 times pi, and that would be our particular volume there. And the measurement would be certainly, we could look at this and consider this to be likely cubic feet because of the units that we've been dealing with here. So part F is another homework assignment that we're going to give you. It's a wonderful way to connect everyone's favorite AB topic, related rates, into this idea of a table, and the fact that we have this cross-section idea that segued into this area and volume that we've been doing, but now it culminates in this wonderful related rate problem. All right, Ryan, take over these slides, and let's put an ending to this wonderful week that we had with our tweets.
Yes, absolutely. And Tony's going to read the tweets off to us. I want to remind people, Tony, as you're ready to do that, our Twitter accounts are on there. We love hearing from you. Whether it's telling us about your awesome AP teacher with the hashtag, whether it's telling us about your awesome AP students with the hashtag, or whether it's talking about your pet, your dog, or your cat, or sending something to us, or we've got so many tweets of students and teachers saying you've been with us every day, right? We want to hear those things because it really energizes us, and we love to connect with you. So look at that. Let us know what you think. Let us know what your favorite parts of the lessons are about your dog, sometimes all kinds of things. And if you want a little teaser for next week, I'm gonna have a little theme next week because Tony, you and I were talking recently about how you got a haircut, and I need a haircut, but nothing's really open. And so I started wondering what's happening with all that. Are you getting haircuts? And my nephew, who's home from college, Tony, let me cut his hair the other day. I had to pay him to do it, by the way, but I cut his hair, and so I started a new segment called Worst E-Learning Haircuts. Did you get a bad haircut? Is mom or dad or friend trying to cut your hair didn't work out right? Well, my nephew's hair is pretty atrocious, so I've got some photo evidence next week. But I want to hear from you. Did you or anybody else have a distance learning bad haircut? So Tony, with that said, what do we have for our tweets today?
Our 2 tweets are going to recognize a couple of friends of Ryan and I that happen to be consultants with the College Board and work really hard, and we've known them for a long time from the reading and so forth. So for our AP Teachers Rock, special shout out thanks to Sister Alice Hess, my BC and Stat teacher, for always doing what she can to help us out and make sure that the class is prepared. So Sister Alice, if you are watching, we're definitely thinking of you, and we certainly miss not seeing you here at the reading and various consultant events. And for our AP Students Rock, so proud of the AP students at Flushing High School who are working hard and are focused on the upcoming exam, missing their faces every day. Raider Nation's greater than quarantine. And this is our good friend from Michigan, Karen Sino. And so we want to make sure that Miss Sino gets a nice recognition there, and she's doing great things with her students. And I know they love having her as their teacher. All right, and our exam is coming up, right, Tony? And we'll talk more about that later. So don't panic. Why don't we talk about that? Because as we get closer, we'll be much more focused on that. And Tony mentioned this is our upcoming problems. And Tony, you mentioned this, but I want to just reiterate this. We got our problem types next week, which is going to be awesome. But we are on for an extra week. These were originally going to stop on May 1st because the exams were going to start on the 4th. But now the exams are starting on the 11th, that final week from May 4th to May 8th, right? We will be here live as well, doing even more great proper to get you ready. So the device information is on there if you need to get a hold of that. But then the pet of the day, we've got so many entries, Tony. It's been crazy how many pictures of people's pets we've been getting. So if you have them, I didn't get them today, don't worry. I'm going to find a way to get them in. But we have 4 today, Tony. 4 pets a day. I know that you're going to probably add more teacher tweets and student tweets. We're getting so many great submissions. We want to recognize those teachers and students. But here's what we have today, kind of going across the board. So we got Chase, the cat, from our friend Ella, and then we have Jack, Zach, the dog. And this is funny because I said you can call Jack or Zach, but he doesn't really answer to either one of them. So thank you, Christina, for doing that. And then nice little Harry Potter reference. Maybe that's why I made the Harry Potter local visibility reference. It was a subconscious thing when I saw this. But Hermione Granger is another great one. Hermione's from a teacher, and Hermione helps the teacher grade their papers and record all of their lessons each day. And then the late dog Hannah from Jill, another teacher. This is a pretty smart dog. He's pretty engrossed on this, but Hannah passed away. But we wanted to make sure we recognize Hannah for all of her awesomeness. Again, our Twitter handles are on the bottom because we want you to reach out to us. Let us know about your dog, your teacher, your students, your bad haircut, anything else, right? You've been here every day. Tell us. We'd love to hear it. So any final thoughts, Tony, as we head out? I'm glad that we've been able to pick up another 5 episodes. So we have 10 more days with you. We're excited about putting those things together and just get you guys more and more prepared and more confident about the 80s. And that's what our job is, and that's what we were going to do. So great week. We'll definitely see you Monday.
Yes, have a great week, Tony. See you Monday, guys.
Stay safe, keep learning, guys.
AP Calc, yes, AP Calc. Welcome to AP Calc, yes, AP Calc.